So you've heard that TensorFlow is one of the most in-demand skills for machine learning engineers, and now you want to get up to speed fast. Well, thank the YouTube algorithm or your elite search skills because you've landed in the right place. This crash course is your hands-on intro to building deep learning models with TensorFlow. You'll start with the fundamentals, then move on to neural network regression, classification, computer vision, and even transfer learning using pre-trained models. And yes, you'll actually build real models, not just watch someone else do it. Your guide is none other than Daniel Bourke, a self-taught machine learning engineer who's worked at Max Kelsen, one of the fastest growing AI agencies in Australia. And he also has an extremely popular YouTube channel of his own. By the end of this crash course, you'll understand how TensorFlow works and how to build and train basic deep learning models, a solid first step into becoming a TensorFlow developer. And here's something extra for those of you taking this crash course. As a massive bonus, we're given direct access to ZTM's community Discord, which is typically reserved for ZTM Academy members. This means that you can now chat with others taking the exact same course as you, ask questions, and even get feedback from Dan himself. The invite link is in the description down below. Alright, that's enough chit chat for me. Let me hand it over to Dan so you can start learning TensorFlow. Enjoy!
Alright. Are you ready? I hope you are, because we're about to learn deep learning with, wait for it, TensorFlow. Now we could go back. I want to watch that again. Deep learning with TensorFlow. Now, if you like that little animation, that's just a taste of what to come, because we're going to have lots of fun learning deep learning with TensorFlow. Now, if you're here for that, you might be asking yourself the question, what is deep learning? Well, for these type of questions, and you'll probably notice this trend throughout the course. Oh, we've come to our friend Google here. What is deep learning? Oh, there we go. A type of machine learning based on artificial neural networks in which multiple layers of processing are used to extract progressively higher level features from data. Whoa, there's a lot going on there. You might be thinking, Daniel, why did we go straight to Google at the beginning of this course? Well, for questions like this one, where there's some sort of definition, this is what I want you to do. If you're not sure what it is, I want you to search for it and do some research, because what we're going to be focused on in this course is getting hands-on as quick as possible. So we're going to be writing lots of code. So let's come into my definition of machine learning for this course. Machine learning is turning things, data, into numbers and finding patterns in those numbers. And you might be thinking again, now Daniel, I've signed up to this deep learning with TensorFlow course. Why have you got machine learning there? Well, we'll answer that question in a second. But in terms of finding patterns, how does this happen? Well, the computer does this part. How? Code and math. Now, we're going to be writing lots and lots of code to do this. More specifically, code or deep learning code with TensorFlow. So let's have a look at machine learning versus deep learning. We have this fun little diagram that you might also find on Google. There we go. Artificial intelligence. Artificial intelligence, machine learning, deep learning. There we go. Very similar one here. So if we have the broad field, that is artificial intelligence. So trying to get a computer to think for itself. And now if we have machine learning, which comes under artificial intelligence, remember the definition for machine learning from before was writing code for a computer to figure out patterns in data. Well, deep learning is usually considered a subfield of machine learning. And so this is about all you need to know for the time being. I mean, if you want to do your own research, what deep learning is, go ahead and do that. But again, with this course, we're going to be focused on getting hands-on writing deep learning code. So if we come here, what's the difference between traditional programming versus machine learning or deep learning programming? So with traditional programming, you might start with some inputs. You might code up a bunch of rules. In our case, we've got our favorite Sicilian grandmother's chicken dish here. And she's got this recipe. And she knows it off by heart, and she's passed it on to you because you want to host a dinner party at your place and invite everyone over. So you might start with the inputs, which are the ingredients. We've got some vegetables here. We've got the chicken, of course, and we've got the rules. This is what we have to do. Cut the vegetables, season the chicken, preheat the oven, cook the chicken for 30 minutes, add vegetables. And then if you've done all this correctly, you'll get this beautiful output. But where machine learning algorithms usually differ is that you'll start with the inputs and the ideal output. So this is the major difference here. We're going to be very familiar with this concept of inputs and outputs by the end of the course. And so what happens with a machine learning algorithm is you'll show it examples of what the inputs look like and what the ideal outputs look like. So this is a beautifully cooked chicken here from this input. So you'll start with this, and then the algorithm will figure out, hopefully, the ideal rules to get from this input to this output. All right, so that's the machine learning in a nutshell. The next video, we're going to cover why use machine learning or deep learning. So now we've got a little conceptual overview of deep learning, very brief. The next question to answer is, why would we want to use machine learning or deep learning? So the good reason is, why not? I mean, you might have seen what machine learning is capable of. You might have heard of the power of deep learning, the power of artificial intelligence, and just all the problems we've got in the world. Why not we just use it? Maybe. But a better reason is, for a complex problem, such as maybe we're trying to teach a self-driving car to drive, can you think of all the rules you'd have to code if we remember back to our Sicilian grandmother's famous chicken recipe? Maybe you can code up the rules for that, such as preheat the oven, cut up the vegetables, cook the chicken for 30 minutes. But in terms of a self-driving car, when you go for a drive, do you think about the rules in your head, or do you just drive? You'd need stop signs, you'd need traffic lights, you'd need what to do for another car. You can imagine how that problem gets quite out of hand pretty quickly. So for a complex problem, can you think of all the rules? Probably not. And so I found this great comment on one of my YouTube videos here, the 2020 Machine Learning Roadmap. So be sure to check that out if you haven't checked it out. This is from Yashawi. I think you can use ML, so machine learning. If you see ML throughout this course, it's machine learning, for literally anything as long as you can convert it into numbers and program it to find patterns. Literally. It could be anything, any input or output. Oh, we've seen that again, input or output from the universe. Wow. Important piece to note here is as long as you can convert it into numbers. Now again, if you're reading this and you're like, Daniel, this doesn't make sense. I've never experienced deep learning before. Don't worry. We're going to have plenty of practice throughout the course. But here's the exciting part. I think you can use ML for literally anything as long as you can convert it into numbers. I want you to keep that sentence in your head. However, when should you not use machine learning? If you can build a simple rule-based system, or actually maybe not very simple if you're building a complex software product that doesn't require machine learning, do that. Where's this come from? Well, this is from a very wise software engineer. It's actually Rule 1 of Google's Machine Learning Handbook. So this is our first external resource for the course. There's going to be a bunch of these, so don't worry. I'll link them to wherever you need them. So this is the rules of machine learning. Best practices for ML engineering. We're not going to go through this, but I'm going to link to this. If you want to read through this in your own time, feel free to do so. This is a very exhaustive resource to get you up to scratch on how Google thinks about using machine learning. So we'll come back. So yeah, if you think about using machine learning, but you think you can code up a simple rule-based system, you should probably do the rule-based system rather than machine learning. So what is deep learning good for? Problems with long lists of rules. So when the traditional approach fails, machine learning/deep learning, again, whenever you see throughout this course machine learning/deep learning, you can kind of think of them as the same thing, may help. Continually changing environments. So if the problem you're trying to solve is constantly changing, the information you're dealing with is continually changing, The good thing about deep learning is that it can adapt to new scenarios. So if the problem you're working on changes, you can train another deep learning model on those changes. Discovering insights within large collections of data. So imagine the problem of trying to take photos of food and identify what's in that photo. Can you imagine trying to handcraft the rules for 101? So you just wanted to start with, you were building an app called 101 dishes. So you've got maybe spaghetti, ramen, steak, eggs, kale, coffee. Can you imagine trying to handcraft the rules for what 101 different kinds of food look like? I can't. Now, what is deep learning not good for? Typically, again, take this with a grain of salt because as you'll see, as you get deeper into your, pardon the pun, deeper into your deep learning journey, you'll see there are lots of ways, if you're stuck on a certain problem about what we're about to see on this slide, you can kind of formulate ways to circumvent that problem. When you need explainability. So the patterns learned by a deep learning model, again, we haven't seen these, but we will get familiar with them, are typically uninterpretable by a human. So if a deep learning model is finding lots of patterns in numbers, which we'll see throughout this course, typically those patterns are quite hard to interpret once you look at them. When the traditional approach is a better option, remember, if you can accomplish what you need with a simple rule-based system, you should probably do that. When errors are unacceptable. So since the outputs of a deep learning model aren't always predictable, meaning they may contain errors, maybe deep learning isn't your best option. If you need a software system to do the same thing every single time, potentially a non-deep learning based system is what you're after. And when you don't have much data, so deep learning models usually require a fairly large amount of data to produce great results. However, we'll see how to get great results without huge amounts of data. So as I said, typically not good for. There are ways to kind of try and circumvent these points here. So let's have a look again. Machine learning versus deep learning. So in terms of when to use machine learning versus deep learning, traditional machine learning algorithms have typically performed best on structured data. So what I mean by structured data is data or information you can find in an Excel spreadsheet or a Google Sheets. So you've got rows and you've got columns. So this is clearly row 2, for example. We've got car sales, we've got a make, we've got a color, we've got odometer, doors, and we've got a price. So maybe we want to build a deep learning model or a machine learning model to take these parameters here, which are often referred to as features. So columns, features, make, color, odometer, doors, and predict the price. Whereas deep learning typically performs better on unstructured data, such as natural language text, or in the case of we wanted to build our Food 101 application to take photos of food and identify what's in that food, or if we have a Wikipedia article talking about deep learning. So this is an example of data that you could argue that there is structure to this picture. Like, I mean, you got a shape here, you got shapes there, and here you've got a sentence there, but it's certainly nowhere near as structured as what you find in an Excel spreadsheet. And then again, you could have something like voice, so sound waves. If we go here, we'll dig a little deeper into the structured versus unstructured data. Let's have a look at some of the most common algorithms you're going to come across in the machine learning and deep learning world. Of course, this slide only goes through just the names of the algorithms, but we're going to be getting hands-on with building some of the most common deep learning algorithms you see coming up in a minute. So on the machine learning side of things, you might have the random forest, the naive Bayes, nearest neighbor, support vector machine, and many more. And since the advent of deep learning, these algorithms here are often referred to as shallow algorithms. Now, what that means for now is not too important. I just want you to start getting familiar with some of the terms you're going to hear in the machine learning and deep learning world. So when they come up, you're not going, wow, what does this mean? Now, on the deep learning side of things, we have neural networks, fully connected neural networks, convolutional neural networks, recurrent neural networks, and the transformer architecture is a fairly new one that's only come out in the last couple of years. And for this course, we're going to be focused on building these 4 type of neural networks here with TensorFlow. These are kind of like the bedrock type neural networks, the ones that a deep learning field over the past decade or so has been built on top of. And again, if we're looking at through the structured data versus unstructured data paradigm, these algorithms here, the machine learning algorithms, are typically better performing on structured data, whereas neural network type architectures are typically better performing on unstructured data. However, depending on how you represent your problem, many algorithms can be used for both structured data or unstructured data. Now, we've covered the names of a few types of different neural network architectures. So you're probably wondering, or the question in your head is probably, what exactly are neural networks? So let's tackle that in the next video. All right, so in the last video we heard that neural networks are a common deep learning algorithm. So what exactly are neural networks? So remember, for these type of what questions or definition questions, I want you to get really familiar with going in, what are neural networks? Explained, neural networks. Neural network, okay, Wikipedia. These are generally quite wordy definitions. A neural network is a network of circuit or neurons, or in a modern sense, an artificial neural network composed of artificial neurons or nodes. So you might get diagrams like this. And so that's just a one-sentence definition, but let's have a look of an overview of what neural networks are. So we might start with some data here, whether it be images of food, or some natural language text, or some sound waves, like what's going into the microphone here. And then if we want to use that data with a neural network, we're going to have to somehow turn this into numbers. So this is called a numerical encoding. There are many different names for it, but we're going to treat this as a numerical encoding. And you might be wondering, what are these square brackets? Well, that's to represent that we've got this data here, and we've turned it into a numerical encoding, which is often referred to as a tensor, but we'll see that. We're getting ahead of ourselves here. And so before data gets used with a neural network, it needs to be turned into numbers. Okay, remember our one-sentence definition of machine learning. Machine learning algorithms are about turning data into numbers and finding patterns in those numbers. So this is our numbers here. Now we might feed these numbers here that represent our data into a neural network. If we come here, this is a simple neural network. This is a very similar diagram here, but probably a little bit more colorful. And what is this neural network going to do? Well, it's going to learn a representation, all the patterns, features, weights. These are other terms you might hear of what kind of representation it learns. And again, depending on what problem we're working on, whether it's recognizing images or discovering meaning from text or trying to turn a sound wave into text, you're going to have to choose the appropriate neural network for your problem. We'll see how to do that in upcoming lessons. So this is, okay, we've got 3 steps so far. We've got data as inputs. We've turned that data into numbers. We're going to feed that to our neural network, and this is going to learn a representation or find patterns in these numbers. What does it do then? Okay, then it's going to create some representation outputs. You might notice that these numbers have been transformed. And so this might not mean anything to us now. We're going to inspect this in a moment with TensorFlow code. But what these representation outputs are basically the neural network going, you know what, I've taken in these numbers here. I've found the patterns. These are the patterns that I've found in a numerical representation form. Okay, all right, and then what do we do next? Well, it's up to us to take these representation outputs that our neural network has learned about our data and convert them into human understandable outputs. So say, for example, in classifying images of food, we might have a photo of ramen here, might have to turn that into numbers in some way, might have to feed it through our neural network, and get our neural network to discover patterns in that, so it outputs into a representation output. And then it's our job to write some code to convert these representation outputs to hopefully, if it's learned it right, it's going to output the label ramen. And the same goes for this photo of spaghetti. We could pass that through and it goes to there. And maybe for this tweet, we want to say we're building a system that was to read a tweet, and say we wanted to know where natural disasters are going on in the world. Can we convert this tweet into numbers, feed it through a specific type of neural network, convert it into some sort of representation output, and then label it as, say, a disaster-based tweet or not a disaster? And then finally, say we're building a smart speaker or something to recognize sound waves. How would we turn those sound waves into numbers? Pass it through our neural network, get our neural network to discover patterns in those numbers, create a representation output, and then translate or transcribe, I think transcribe's a better word there, transcribe that to, hey Siri, what's the weather today? Whoa, there's a lot going on here. But again, this is the whole premise of neural networks here. We have some inputs, we turn those inputs into a numerical encoding. Our neural network that we've chosen for our specific problem will learn a representation referred to as patterns, features, or weights. We'll create some kind of representation output based on the patterns it's figured out, and then it's up to us to define what we want our outputs to look like based on this. So let's look at the anatomy of a neural network. So if we have it here, the first layer of a neural network is referred to as the input layer. So when you see diagrams like this is actually a very common diagram of what a neural network is. If we go here, neural network, back, what are neural networks? There we go. So we have inputs, something in the middle, outputs. Remember in our previous slide, our input, the data goes in here. In this case, this would be labeled with, these are two hidden neurons. Again, we're going to get very familiar with these terms as we keep going. And in the middle here, there's hidden layers. You'll notice this is a plural. So usually there's one input layer, or depending on what data you work with, you might have multiple input layers. Hidden layers, this can be an arbitrary amount of layers. So you could have one hidden layer, or you could have 152 hidden layers. So these hidden layers learn the patterns in the data. And then it has an output layer. So this outputs the learned representation or prediction probabilities. Again, we're going to get very hands-on with all of these terms. I don't want you to get too flustered with the terms that I'm putting out here because we're going to see all of these in action. And in this case, with the input layer, there's two neurons, and there's three hidden neurons here, and there's one neuron in the output layer. And I want to put a little tidbit here, is that when I say learns patterns in data, it's kind of an arbitrary term because you're going to hear lots and lots of jargon and different terms for different things in machine learning. And I'll try use as many different terms as possible, but also tie them back to kind of a single term. So when you hear me saying patterns, you'll often hear different things like embedding or weights or feature representation or feature vectors. And these are often all referring to very similar things. Now, when it comes to neural networks, we've seen the anatomy, but there's also a few different types of learning. The first one is supervised learning, semi-supervised learning, and then unsupervised learning, and transfer learning. Whoa. And so supervised learning often involves having data and labels. So in the case of identifying different images of food, we may have the data would be the images of the food, and the labels would be the labels of food. So ramen, spaghetti, coffee, steak, pizza, associated with each one of those images. Semi-supervised learning has some data, or actually could be as much data as supervised learning, but it only has some labels. So, for example, maybe we had 10,000 images of food, and we only had labels for 1,000 of those images. And we wanted to train a neural network on the images which have labels. And then we use that neural network to try and label the other images of food, the ones we don't have labels for. And then unsupervised learning is you basically only have data and no labels. You kind of pass your data to a machine learning model or a neural network or a deep learning model. Again, very similar terms for very similar concepts. And you kind of go, hey, I'm not sure what patterns are going to be within this data, but see what you can find anyway. And then transfer learning, which is actually a very, very important concept. We're definitely going to get hands-on with this one. The beautiful thing about deep learning models is when they learn patterns in some sort of data set, those patterns can be used for another problem type. So transfer learning would be taking what one deep learning model has learned on some set of data and then using it in another problem on another set of data. So in our food image discovery or image classification problem, we may take what a machine learning model has learned on just pictures of the world, so general pictures, and apply that to our specific images of food. Now, in terms of this course, we're going to be writing lots of code to do supervised learning and transfer learning. But again, the premise of what we're doing, starting with inputs, turning that into numbers, and then having some sort of algorithm go through those numbers, find patterns, create outputs, can also be used for these other two types of learning here. All right, so now we've heard a little bit about deep learning, we've heard about neural networks. What is deep learning actually used for? Now, what is deep learning actually used for? Well, we'll return back to this comment we saw before, because this is actually a beautiful comment. Thank you very much, Yashui. Hopefully I'm saying that right. I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. Literally, it could be anything, any input or output. Again, lots of emphasis on input or output from the universe. And so I want you to keep this sentence in your mind, because by the time you finish this course, you're going to look at the world through a different lens. I mean, you're going to walk down the street and you're going to wonder, how could I represent this experience that I'm having in numbers and then program a machine learning algorithm or a deep learning algorithm to find patterns in those numbers? Seriously, once you learn the concept of machine learning and deep learning, you start to look at almost everything through the lens of turning something into numbers and finding patterns in those numbers. Now, let's have a look at some common deep learning use cases that you've probably experienced in your day-to-day life. So the first one is recommendation, translation, speech recognition, computer vision, natural language processing. Again, emphasis on some here because there's many more, but these are some of the main ones. So the recommendation here, this is my YouTube home screen. We've got some programming videos. We've got a video of my friend's YouTube channel, an interview from Peter Norvig, one of the heroes of artificial intelligence, some RuneScape videos, because that was a game I love to play, jiu-jitsu, some bodybuilding. Oh my goodness, more hacking videos. So I can safely say YouTube has learned me pretty well. And now this is based off, again, my history of the things I've watched on YouTube. And so if YouTube has all of that information, it can go, you know what, Daniel, I've seen 100 different people, or maybe in the case of YouTube, there's actually close to, I think, over 1 billion users on YouTube. Maybe there's 100,000 people out there like me. And they're like, you know what, you've watched programming videos, so we're going to show you this one. And you're interested in the movie Her, great movie, by the way. We're going to show you this soundtrack based on the patterns that we found in everyone else's YouTube browsing history. And then in the case of translation, we might have some language here. This is English, the language that I speak. And if I wanted to speak Spanish, I'm not even going to pretend that I can pronounce that. I can type in my sentence here, deep learning is epic. And then Google will run a deep learning algorithm to figure out the patterns in this English sentence and translate that into Spanish. So if you're a Spanish speaker out there, you can tell me or send me a message of how accurate this translation actually is. In the case of speech recognition, we may have some sound waves, again, like what I'm saying here. And when I find out from Siri, it's like, hey, who's the biggest big dog of them all? And so deep learning probably go through that sound wave and transcribe it into this sentence here. Computer vision. Actually, this image is a bit painful for me because this is actually from some security footage from one of my neighbors. You see this car here? If I had a computer vision algorithm that was running on this security camera, maybe I could pick up this car or found the license plate, because this car, actually, the trailer, it had a trailer on the back. The trailer came off as it was driving past my car on the street, and the trailer hit my car and basically totaled the whole car. So now I need to find a new car, and this was the car that did it. So if their security footage had a computer vision algorithm, maybe we could have found it. So I'm still on the investigation for that, but that's one use case computer vision can be used for. So again, a deep learning algorithm may take the pixels of this image, find the patterns and go, you know what? I've seen a car that looks like this before. Maybe it's a Toyota Hilux that you're looking for. Anyway, we'll leave that problem there before I get too upset. I really loved my car. And the other one is natural language processing. So maybe taking in an email, you got your text here. So unstructured text here. Hey, Daniel, this deep learning course is incredible. Oh, thank you so much. I can't wait to use what I've learned. I hope you send me a lot of these type of emails here. That is my actual email address, so feel free to send me whatever you want. And this is not spam, so this is something I want to see in my inbox. But if you're sending me messages like, hey, Daniel, congratulations, you win, that is a big number. I'm not going to pretend that I can read that out loud without slowly deducing how many zeros there are. That's spam, so I don't want this in my inbox. I want a natural language processing algorithm, a deep learning algorithm, to put that in my spam box. And so if we dive a bit deeper, you might see these referred to as sequence-to-sequence, or sec-to-sec for short, deep learning problems. Now, the premise here is if sequence-to-sequence doesn't make much sense, just think about it like this. You have a sequence of words and you want to translate or transform that into another sequence. That's what you're trying to do with seek-to-seek problems. Same with here. You might have a sequence of sound waves and you're trying to convert them into another sequence of words. And for this problem here, it's called classification or regression. Now, classification, is this email not spam or spam? Is it one thing or another? There's also multi-class classification, but we'll get onto that in a second. And then regression, you might be wondering, hey, Daniel, I've heard regression is more so for predicting a number. Yes, well, in this case, in our computer vision problem, our numbers might be the pixel coordinates of where the corner of this box should be. So maybe we start with an image that doesn't have a box on here, and then our computer vision algorithm looks over it, or our object detection algorithm looks over it, and goes, you know what? I think the car is most likely in the box here. So maybe that's 50 pixels in from the x-axis and 60 pixels down from the y-axis there. And so that's that corner, and then it does the same for each other corner. Now, I want to show you another phenomenal use case for deep learning that only just recently happened. So if we go here, now you could also just go deep learning use cases, and you're going to get a whole bunch of different ones. There we go, automatic speech recognition, image recognition, natural language processing. But there's one I'm specifically looking for. Now this is DeepMind. Deep stands for deep learning. Now this is a deep learning research company. Boom, AlphaFold, a solution to a 50-year-old grand challenge in biology. I'm not going to go too much into this, but this is possibly one of the biggest breakthroughs in AI, powered by deep learning, as well as, do I want cookies? Fine, I'll have the cookies, as long as they're delicious. Now, do we have deep learning here? Here we go. Now, new deep learning architectures we've developed have driven changes in our methods for CASP14, enabling us to achieve unparalleled levels of accuracy. Again, I'm not going to go too deep into this, but this is the type of, I believe they've used a deep learning algorithm. This is actually brand new, to figure out how a protein should fold. Now again, I haven't read up on the research here, but this is just the type of things that deep learning can be used for. If you remember the comment we looked at before, the YouTube comment, I think you can use ML for literally anything as long as you can convert it into numbers and program it to find patterns. So that's what DeepMind have done. They've taken proteins, turned them into some sort of numerical representation, crafted a deep learning architecture to find patterns in those proteins. So this just blows my mind. As I said, by the time you finish this course, you're going to have a new lens on the world. So we've seen what deep learning can be used for. How can we write these deep learning algorithms? So this is where TensorFlow, that's worthy of seeing again, TensorFlow comes in. So in the next video, let's figure out what TensorFlow is. We've seen that deep learning can be used for a range of different problems, including how deep learning architectures are now figuring out the protein folding problem. In other words, finding patterns in proteins. I mean, proteins as in the building blocks of you and I. So if proteins are the building blocks of you and I and deep learning is finding out patterns in that, how might we create such deep learning architectures? And if you see deep learning architecture, deep learning model is kind of another word that you can substitute in here for architecture. So when you see deep learning architecture, you can think deep learning model. And when you think deep learning model, you can think deep learning architecture. So how might we build such a thing? Now, this is kind of a segue to TensorFlow. The TensorFlow is going to help us build deep learning architectures or deep learning models. And now, of course, naturally, you're probably asking, well, what is TensorFlow? Let's figure this out. TensorFlow is an end-to-end machine learning platform. You can write fast deep learning code in Python, which is the language we're going to be using, / other accessible language such as JavaScript. And when you write that fast deep learning code using TensorFlow, that code is able to run on a GPU, which is a graphics processing unit, / TPU, which is a tensor processing unit, hence TensorFlow. We're going to see the significance of that in a moment. With TensorFlow, you're also able to access many pre-built deep learning models. When we saw types of learning, transfer learning is where you'll use a pre-built deep learning model. In other words, leveraging the patterns that one deep learning model has learned on another problem to your own problem. We'll see how we can use TensorFlow Hub to do that, which is a TensorFlow resource. Now, it's the whole stack. This is a follow-on from this point here. TensorFlow allows you to pre-process data. In other words, turn that data into numbers, model that data. In other words, build a neural network to find patterns in that data, and then deploy your model into your application. So depending on what you're building, you might want to take the deep learning model, such as in the case of our security recognition system, if we wanted to identify different types of cars, we might want to take our computer vision model and deploy it into our security camera and use that to detect cars that have maybe crashed into other cars. In my case, again, you can probably hear the sadness in my voice. It makes me emotional when I talk about my poor little car. And it was originally designed and used in-house by Google, one of the largest internet companies in the world right now that basically machine learning runs everything that they do, machine learning and deep learning. And it's now open source, which means we can leverage the tools that Google use to work on our own problems. So that's a bit of an idea of what TensorFlow is, but why TensorFlow? Well, it allows us easy model building. Now, again, this is from the TensorFlow website. We're going to get very familiar with this website. Robust ML production anywhere. So train your models, deploy them in the cloud, on-prem, which means on your server if you have one locally, in the browser or on device, no matter what language you use. Powerful experimentation for research. So if you found a new idea, such as DeepMind building a new deep learning architecture to discover patterns in protein folding, you might want to rebuild their research using a TensorFlow-powered deep learning model. And so we're going to be doing lots of this, easy model building. And we're also going to do a little bit of this throughout this course, but that's for later on. In the meantime, let's check out the tensorflow.org website. So here we go. An end-to-end open source machine learning platform. There's a lot going on here. So you've got some examples here. You can see, you can install it, you can learn it. There's the API. Probably the exercise for this lesson is to go to tensorflow.org and have a play around. Just get yourself familiar with the website. If you've never looked at this website before, there's probably almost too much here, so it can be a little overwhelming, but that's all right. Just follow your curiosity and see what's there. Let's go back here. Now, why else might we want to use TensorFlow? Now, this is Francois Chalet, and this is a tweet that he put out recently. With tools like Colab, we'll get familiar with Colab, Keras is a part of TensorFlow, and TensorFlow, virtually anyone can solve in a day with no initial investment, so that means basically for free, problems that would have required an engineering team working for a quarter is 3 months, and $20,000 in 2014, which is so true. So the resources we're going to use throughout this course, I mean, just 5 years ago, or just a little bit over 5 years ago, would have cost a fairly large amount to even get up and set up. And not only like the things that we're going to be doing ourselves, would have required a whole team working for a couple of months that we're going to be getting up and running within, in some cases, a few lines of code. So this is why it's really, really exciting to be able to use TensorFlow and these other resources here to work on deep learning problems. So now, we mentioned before, TensorFlow allows you to run your numerical code on a GPU/TPU. Now, what exactly is a GPU/TPU? If we come here, this is what, if you Google the photo of a GPU, you'll get up this, graphics processing unit. These are actually NVIDIA cards. This is an RTX 3080, and I believe this is a P100. So you don't need to worry too much about these. You can install these in your own computer, like these type. These are usually built for servers. Say you have like a warehouse of different computers. This is often what you'll get when you connect to a cloud-hosted GPU, but we're getting a little bit too ahead of ourselves. The major thing you need to know about these graphics processing units is that they're very fast at crunching numbers. So when I say we want to find patterns in numbers, these type of computing chips are very fast at finding or doing numerical calculations. In other words, finding patterns in numbers, the numbers that we've converted our data into. And in the case of TensorFlow, it also allows you to use TPUs, which are tensor processing units. Now, this looks like a pretty advanced piece of hardware. If we go here, what is a TPU? Again, for these questions where you have what is something, don't be afraid to look it up. Tensor Processing Unit. Whoa. Tensor Processing Unit is an AI accelerator application-specific integrated circuit developed by Google specifically for neural network machine learning, particularly using Google's own TensorFlow software. Ah, okay. So this is what we're going to get familiar with. And so if you think of a TPU, if graphics processing units are fast at crunching numbers, well, a TPU is probably even faster. But we're going to see throughout this course how we can get access to these chips. If you don't have, I mean, unless you're Google, you probably don't have this in your computer right now or in your bedroom or something like that. You maybe not even have one of these, but that's okay. We're going to look at resources throughout the course that we can use to gain access to these fast computing chips for free. Now, we've heard a lot about tensors, or specifically TensorFlow. And naturally, you might be asking, what is a tensor? So let's look at that in the next video. We've seen TensorFlow, discussed what it is and why we should use it, but we haven't actually discussed half of its name. I mean, what exactly is a tensor? Great question. Now, remember our slide for neural networks? I'm going to give you a little hint. Oh, we kind of revealed this earlier, so spoiler alert. Remember how we started with our inputs, which is maybe some images, maybe some natural language text, maybe some sound waves, and then we create a numerical encoding. We pass that numerical encoding to our neural network, which learns patterns in that numerical encoding. And then our neural network outputs some kind of representation outputs. And then we convert those into something that we can understand. Now, the secret here is that these are tensors. Whoa. And so the most basic definition I can think of for a tensor is some way or some numerical way to represent information. Now, what that information is, I mean, that's totally up to you. But just think of it as if we wanted to encode these images into some kind of numerical form, we're going to be turning them into a tensor. and we're going to see this in practice as we write TensorFlow code, we're going to pass that tensor to our neural network. Our neural network is then going to figure out different patterns in these numbers, and then it's going to output another tensor, which is the patterns that it's learned in our original numerical encoding. And then we take this tensor, the representation outputs from our neural network, and convert them into something that we can understand. So if we take away some of the excess parts, this is the founding principle of neural networks and tensors in general. I mean, this is where the name TensorFlow comes from. If we imagine our inputs, our food image classification problem, we turn it into a numerical encoding, in other words, a tensor. We pass it to our neural network. Our neural network finds the patterns and then outputs those patterns that it's found, and again, this is another tensor, into something that we can understand. So if you imagine, this is the flow. This is where the flow in TensorFlow comes from. It starts here by creating a numerical encoding, then it flows through our neural network, then our neural network flows it on again, the output here, and then we, again, another little flow here into something that we can understand. So that's what you have to understand for the concept of tensors. If you want a little bit of an extension, I'll show you one of my favorite videos on what is a tensor. This can actually be your homework. Is this video here. So this is available on YouTube. What is a tensor? So I want you to watch this video, figure out Dan Fletcher's, I'm not quite sure how to pronounce that name, but Dan, also a great name. Watch Dan's explanation of what a tensor is, and then come back to the other Dan, me, and then see if you can line these up. Remember, a tensor is a way to represent some sort of data in numerical form. So if we come back, we've covered what TensorFlow is, we've covered what deep learning is, we covered what neural networks can be used for. What else are we going to cover? We'll look at that in the next video. We've covered a fair bit in this course already, but let's get specific. What are we going to cover throughout this course? Well, I have a great tweet here from Elon Musk, Dose X Machine Learning. So learning ML, or machine learning, deep learning from university, you get this small little brain here. Online courses such as this one, you get some activation here. From YouTube, whoa, we're really starting to activate the brain here. From articles, look at that superpower. And then from memes, I mean, this little figure here looks like they can control the whole universe. So we're strictly going to be focused on learning deep learning through memes. No, I'm kidding. As fun as that is, here's what we're going to cover. Now, this is pretty broad, but this is just like sort of a list of the topics we're going to look at. TensorFlow basics and fundamentals, pre-processing data, in other words, getting it into tensors, so turning it, say, from a picture into a tensor. Building and using pre-trained deep learning models. We're actually going to be building our own, a lot of them from scratch, and then we're also going to be using pre-trained deep learning models. Fitting a model to the data, so in other words, learning patterns, so fitting the models that we build and even pre-trained deep learning models to the data we've pre-processed. We're going to make predictions with our models, so using the patterns that our deep learning models have used. We're going to figure out how we can evaluate those model predictions. So if we were building a food classification app and our deep learning model took a photo, we took a photo of pizza and it identified it as steak, and it did that 1,000 times, how can we evaluate our model's predictions to better understand them and figure out how we can improve them going forward? We're going to see how we can save our model and load it, such as if we trained a food classification model and we wanted to use it in our application, we might train it somewhere and then save it somewhere else so that we can use it later on. We're going to figure out how we can use a trained model to make predictions on custom data. So the custom data here is important, because a lot of the time you'll practice training deep learning and machine learning models on data sets that have already been created for you. But the real test of where a machine learning or deep learning model, whether it performs well or not, is on data it has truly never seen before. We'll get familiar with this as we go on. And how are we going to go through all of this? Well, we have the cook, And we have the chemist. Chemist, you can imagine, is very exact. Everything has to be millimeter precise or milliliter precise if you're doing some sort of chemical experimentation. And then you have the cook. Maybe the cook is your Sicilian grandmother, and she's making this beautiful roast chicken dish that she's made 100 times. And of course she has the rules. She knows it off by heart. But this time she decides, you know what? I'm going to sprinkle a little more seasoning in here. I'm going to try a different set of vegetables instead of the traditional set of vegetables that I use. So the cook is a little less exact. A cook likes to experiment and try different things. And in our case, that's exactly how we're going to go through all of this. We're going to experiment. In fact, that's going to be basically our motto for the entire course is experiment, experiment, experiment. We'll be cooking up lots of code. So if we flip this in, boom, we're going to be building ourselves a TensorFlow workflow. We've seen this before. This is what I want you to get really familiar with, is that getting the data ready, turning it into tensors. Then we're going to learn how to build or pick a pre-trained model to suit our problems using TensorFlow and TensorFlow Hub. We're going to fit the model to the data and learn to make a prediction using our trained model. So prediction is where our model takes some sort of sample and then makes prediction outputs that we can turn into something like, if we fed it an image of a bowl of ramen, what does our model think that image is of? We're going to learn how to evaluate our model's predictions. Then we'll figure out how to improve our models through experimentation. Again, experiment, experiment, experiment. And then finally, we're going to look at saving and reloading our trained models. So with that being said, we know what we're going to cover. How should I approach this course? Great question. Let's answer that in the next video. We've been through a plethora of different what questions. And oftentimes you'll see in online courses and online resources, there's a lot of what going on, like what we're going to be doing. But not so often is there how you should approach this course. So we talked about a lot of different concepts: deep learning, neural networks, TensorFlow, tensors. How should you approach trying to learn these things? Well, here's some guidelines. Write code, lots of it. Follow along. So you're going to see me writing a lot of code, and I'm 100% going to make a lot of mistakes. So follow along if you can, and make the mistakes with me. So our first motto is, if in doubt, run the code. If that doesn't make any sense, if you haven't written much deep learning code before, don't worry, we're going to be writing lots of it. This motto is going to be ringing in your head. As much as you're going to look in the world through the different lens of trying to figure out how machine learning and deep learning can be used with almost any problem in your life, you're also going to be hearing this in your head as well. Explore and experiment. So our second motto is experiment, experiment, experiment. This is a great follow-on. If in doubt, run the code. We want to try as many different things as possible because when we're running experiments, I'm going to emphasize trying a lot of different small experiments. Why? Because that helps us, even if the experiment fails, it helps us figure out what doesn't work. And in a lot of cases, figuring out what doesn't work is often just as helpful or even more helpful than figuring out what does. Because how rare, in terms of anything you've worked on previously, how rare is it that you got everything you needed to do correct the first time? And especially in deep learning, I mean, chances are, for the problem we saw, for the deep mind figuring out how to write a deep learning architecture for protein folding, I can only imagine how many experiments they would have done to set that up. Now, motto number 3 is going to be visualize, visualize, visualize. And what I mean by this is if you're not sure of something in the code that we're writing, recreate it in a way that you can understand it. And oftentimes that will be visualizing it in a different way. So say we turn some sort of data into tensors. What do those tensors look like? Can we turn data into a tensor and then turn it from that tensor back into data? Those are the type of things we'll want to be looking at. Now, again, I cannot stress every point on this slide is worth writing down. Ask questions, including I'm going to put inverted commas here. You can't see what I'm doing, but I'm raising my fingers up towards this sky and I'm curling them in as if I'm saying the dumb ones, because there is no such thing as a dumb question. You'll get very smart if you ask lots of dumb questions. So make sure if you don't understand something, you can do exactly what we've done. Go here. What is deep learning? You can search that for yourself. Spend 10 minutes reading here. You'll know a lot more than what you did before you asked the question. Or ask in any of the resources that you have available. So there's the Discord chat, and I'll put some more links in another resource of where else you can ask questions. Do the exercises. So each of the code notebooks of concepts that we have exercises attached to them. So I want to emphasize again, try them yourself, write lots of code before looking at the solutions. Now, this course doesn't cover everything, of course. If this is your first introduction to deep learning, you're going to quickly realize how broad the field is. So if you want to learn more on something, look it up. I want you to become an expert at searching for things that spark your curiosity. Share your work. If you want to learn something, I find, aside from doing it yourself or replicating it yourself, the next best way, or possibly even better, is to teach someone else. So if there's a concept that you've learned in this course and you want to really nail it, you want to get better at it, figure out how you can explain that to someone else. So maybe you write an article sharing how you've learned how to turn data into tensors, write a deep learning model with TensorFlow, figure out patterns in those tensors, and then turn those representation outputs from that neural network into some sort of human understandable output. Maybe you want to share that with others. That's going to be a great way to really cement your knowledge. Avoid the following things. Overthinking the process. So I can't stress enough, this comes back to our number one motto. If in doubt, run the code. Again, we're going to be learning so many different concepts. You're probably going to be overwhelmed at different points, but don't worry. Everyone who's learned anything has gone through the trouble of basically creating new patterns in their brain to understand the new concept that they're learning. So if you're overthinking the process, you're going to hold yourself back. And avoid the I can't learn it mentality. That's bullshit. You can learn it. All right, enough talking. I love that fire. Let's do it again. Let's code. We've got an overview of deep learning. We've got an overview of TensorFlow and tensors. It's time to get hands-on. This is very exciting. So I'm going to open up my web browser. This is the tool we're going to be using throughout basically the entire course, is Google Colab. So if we come here to colab.research.google.com. If you're unfamiliar with Google Colab, check out the Colab overview, or if you just go to colab.research.google.com, you can go to the examples tab here, and you can open up a whole bunch of different tutorials to go through and learn about Google Colab. If you're just starting out, I'd check out overview of collaboratory features or the markdown guide. But as I said, if you want another overview, check out the overview video because we're going to be using Colab a whole bunch throughout this course. So let's get started. I'm going to open up a new notebook here because we're going to, I don't know if you can hear that, but I'm rubbing my hands together because I'm so excited. We're going to get hands-on with TensorFlow. So some of the most fundamental functions of TensorFlow. And let's give our notebook a title here. So let's go 00 TensorFlow Fundamentals. The reason I'm doing 00 at the start is because we're going to, by the end of this course, have probably about 10 or so of these notebooks. So the 00 at the front just lets us know what order they come in. So TensorFlow Fundamentals. And now let's put in here, in this notebook, we're going to cover some of the most fundamental concepts of tensors using TensorFlow. Beautiful. And we can put a little hashtag at the front. And then what I did there was I did Command MM and turned it into a markdown cell. And then if I press Shift and Enter, we get another code cell here. Beautiful. And so to enable us to write code, we're going to have to connect here. So just press the Connect tab there. And let's get a little outline of what we're actually going to do. So More specifically, this is what I do with most of my notebooks. Whenever I come to something before writing code, you're going to hear me say write code as much as possible, but I just like to give myself a little bit of an outline so I know the direction of where I'm heading. So we're going to cover, what do we have? Introduction to tensors. We might as well get some information from tensors. If none of this makes sense, don't worry. We're going to code it up by hand. Manipulating tensors, so changing the information that's stored within tensors. And then we're going to go tensors and NumPy. If you've ever used NumPy, TensorFlow you'll find has very, very similar features to NumPy. Using @tf function, which is a way to speed up your regular Python functions in TensorFlow. Because remember, the whole premise of using TensorFlow is so that we can use GPUs with TensorFlow or TPUs to do faster numerical computing. That's what we're after here. And at the end, we're going to have a few exercises to try for yourself. Alrighty, let's just jump straight in. I'm going to put another little heading here. Introduction to tensors. And then I'm going to press Command MM to turn that into Markdown. Now for another cell here, I'm going to press Command MB. Oh, I didn't press Escape while I had this cell highlighted. So Escape, Command MB will give me a new cell. Now I'm saying Command, however, if you're on Windows, it's probably Control. Because I'm on a Mac, it's Command for me. So the first thing to do is to use TensorFlow is that we have to import TensorFlow. Now, I want you to try and follow along as much as you can with these videos, right? When I'm writing code, I want you to be writing code by my side. It's like we're partner coders here. And if you can't keep up because I'm writing a little bit too fast, that's all right. I've had a lot of practice writing TensorFlow code. And so, again, I've spelled TensorFlow wrong. Maybe you catch my errors before I do. If you need to slow down the video or watch something again, that's perfectly fine. I'm probably going to need to slow down my code so I don't write as many typos. So this is how we're going to import TensorFlow. TensorFlow becomes the alias tf in Python. Tf is basically universal. You can put it as what you want, but use tf, trust me. And then I'm going to use print tf.__ here, version, to check what version of TensorFlow we're using. If you're using Google Colab, you should be using TensorFlow 2.something. I'm currently using 2.3.0. By the time you watch this video, there may be a newer version of TensorFlow, but everything that we do in this fundamentals notebook should still work perfectly fine. So look at that. We've already got TensorFlow ready to go. Now let's jump in and create our first tensor. Creating tensors with tf.Constant. Now you're going to see there's a few different ways to create tensors, but in general, you actually probably won't create many tensors yourself. This is because TensorFlow has many built-in modules, as we'll get familiar with throughout the course, such as tf.io and tf.data, which are able to read in your data sources, such as if you had a whole bunch of different images, and automatically convert them into tensors, as long as you write the code for that, that is. And then later on, our neural network models will process these tensors for us. But for now, we want to get familiar with tensors themselves, so let's start creating tensors. And what I've written here is the word scalar, which you might not be familiar with for now, but that's all right. We will learn what that is. Beautiful. So when we create a tensor with tf.Constant, we get this. We return this. It says tf.Tensor. It has a shape that's empty. The data type is int32. And in NumPy, this value is 7. So again, NumPy and TensorFlow are quite intertwined. Now, if we want to get the information or the doc string for what this function is, in Google Colab, you can press Command-Shift-Space. If you're on Windows, it may be Control-Shift-Space whilst you're in the function. And here we go. Creates a constant tensor from a tensor-like object. Or, if we just wanted to search, TensorFlow tf.Constant. This is what I want you to get really familiar with, is just searching up something like this, and then going into the documentation, tf.constant, yes, creates a tensor, a constant tensor from a tensor-like object. All right. And then we go here, example use cases. So oftentimes, if I'm not familiar with something in TensorFlow, I'll just search it up like this. I'll find the example code here, and then I'll just rewrite that code in the notebook. But let's keep going. Let's keep writing. All right. How about we check the number of dimensions of a tensor? This is another important concept that we're going to get familiar with as we go along. So ndim stands for number of dimensions. You might be wondering, Daniel, what's ndim? So we've got scalar ndim.ndim. Number of dimensions. So 0. Number of dimensions. What does that mean? Well, let's keep going. We'll come back to that in a second. How about we create a vector? So we've got a weird word here you might not be familiar with, scalar. Now, another word you're going to come across quite often in the deep learning world is vector. So let's see what they are. Again, this is the structure of what I want to go through, is write the code first and then go through the concept, or concept code, concept code, concept code. Vector. Let's see how these two differ. We have scalar, which is a TF tensor, has shape, which is blank, dtype int32, NumPy 7. Okay. Now we created a vector, and now we passed it a Python list to tf.Constant, which has TF tensor shape equals 2, maybe that's because there's two items or two objects within this list. The data type is int32, and the NumPy array version is 1010, so the same as this, and the dtype is int32 for the NumPy array version. Okay. All right. Now, what about if we check the dimension of our vector? So we go vector.ndim. What do you think it'll be? 1. Okay. So is that because this shape is empty, maybe 0 came from that, and this shape has 1 element, so maybe that dimension came from that? Well, let's keep going. Create a matrix. So a matrix has more than 1 dimension. Again, if these terms are unfamiliar for now, we're going to get very familiar as we go along. So a matrix, we want to go 10, 7, and then 7, 10. Two of my favorite numbers. If you ever played poker, my favorite hand is 10, 7. Matrix. Let's see what this is. Okay. TF tensor shape equals 2, 2. Does that make sense? 2 items here, comma, 2 items here. Okay, yep, that makes sense. Dtype is int32, so these are integers. And then the NumPy version is just the same thing here with a data type of int32. Wonderful. Now, before I write the code, I want you to have a think. If we write matrix.ndim, if the vector had a dimension or number of dimensions as 1, and if a scalar had number of dimensions as 0, what do you think the matrix will be? 3, 2, 1. Boom. 2. Okay. So I'm starting to see the number of elements in shape is starting to relate. That's where I'm drawing my own pattern between ndim. All right. Now, let's create another matrix, but this time we're going to try out. How about we try and specify the data type? So if we go here, dtype, that's what we want to try and use. So let's try and do that. Create another matrix. Now, another matrix equals, how can we do this? tf.Constant. What do we want to put in? What are your favorite numbers? I'm going to do my favorite numbers again. 10.7. Oh, you might have noticed something different about this one already. So we have a dot after our number. And if you're writing in Python code, what does a dot typically mean after an integer? And 8 and 9. That'll be nice and simple. And then what did we say we were going to do? We're going to use the dtype parameter, float 16. So we're going to specify the data type with dtype parameter. Now, the reason I'm getting you familiar with the dtype parameter is because by default, if we create a tensor with tf.constant, we get the data type int32. So this is known as 32-bit precision. So if we go here, 32-bit precision, which is I'm not going to dive too deep into that. The concept is the higher the number of precision, the more exact these numbers are stored on your computer. So if we do float 16, it's a lower number than 32. So that means storing these numbers or storing this tensor on our computer's memory is going to take up less space. The reason I'm getting you familiar with this is because if you get a data type error in the future of your tensors being the wrong data type, you can manipulate them using the dtype parameter. So let's have a look here. Another matrix. What does this come up as? There we go. Boom. TF tensor. The shape is 3 by 2. Oh, okay. So this is rows, columns. So we have 3 rows. 1, 2, 3. And because we've specified the data type as float 16, we get dtype equals float 16, which makes sense. And our integers here have a dot after, so they're actually floats. And then the same goes for our NumPy version of our tensor matrix. So what do you think the number of dimensions is of another matrix? So if we come back up here, what was our number of dimensions of our matrix here? And our vector and our scalar. We've just created another matrix. If we were to go another matrix dot ndim, what do you think the output would be based on the shape here? Well, let's find out. Boom, it's still 2. So even though the shape here is different, the total number of dimensions, which is the element, I'm really starting to notice a pattern here. The total number of dimensions is how many elements is in the shape. Okay, I've got that down. How don't we see, how might we increase this number of dimensions? I know how we can do it. Let's create a tensor. So typically with this nomenclature, a scalar will have no dimensions, a vector will have 1 dimension, a matrix will have 2 dimensions, and a tensor will have, we'll see what that has. Let's go tensor. Can't reveal all my tricks before we try and code them out. Remember, if in doubt, code it out. Now, to create these, you're going to have to get pretty fancy with where you put your commas. So while I'm creating this, if you're finding that you're like, Daniel, I can't really follow along, that's okay. Just wait till I'm finished here, watch what I'm doing, and then you can pause the video, replicate what I've got, and then we'll run it together, all right? Boom. And then this one has to have 2. Now you see how tedious it is creating tensors from, with your hands? I mean, this is why it's so helpful for TensorFlow to create tensors for us, as we'll see in future modules. Hopefully, I've got all these little square brackets and commas in the right place. So if we look at our tensor, Shift and Enter, what's it going to output? Ooh, hello. We have how many more elements in the shape? We have an extra one. Okay, so there's 3. So 1, 2, 3, yes, 2. So 1, 2, and then 3 again. 1, 2, 3. Ah, beautiful. Now, if we wanted to check the number of dimensions of this tensor, what do you think it would be? I think you might know this one. Tensor.ndim. Boom. 3 dimensions. Wonderful. Now, the important thing to note is that although we've given these different names, tensor, matrix, vector, scalar, is that all of these in TensorFlow, throughout the entire course, we're basically going to continually refer to these, no matter if they're a 3-dimensional tensor or if they're a 2-dimensional tensor, which is a matrix. We're going to consistently refer to them as tensors. So if you're getting confused when I say matrix or tensor, chances are it's the same thing throughout this course. And so, how about we write down some little definitions? What we've created so far. Nice and simple. So scalar, a scalar is a single number. A vector is a number with direction. So e.g. wind speed and direction. A matrix is a two-dimensional array of numbers. Wonderful. And a tensor is an n-dimensional. Now, when you see n, so the n here for n dimensions stands for number. Whenever you see n, it's often referred to as number of something. So n-dimensional means it could be 0-dimensional or it could be up to 1,000 different dimensions or more. Array of numbers where n can be any number, a 0 dimension, as we said before, dimensional tensor is a scalar, and a 1-dimensional tensor is a vector. Beautiful. So that's what we've created so far. We've created our first 5. Have we created 5? 5 different tensors. Now, in the next video, we've created them with tf.Constant. Let's have a look at another way of how we can create tensors, this time with tf.Variable. I'll see you then. So we've created some of our very first tensors, which is so exciting, using tf.Constant. Let's look at how we might do it with our tf.Variable. So, again, little tip here, if you want to create a new cell in Colab, you can press code or text. But most of the time I just do the shortcut, so escape, command MB. Boom. But I'm going to put a text cell here, and I'm going to put a little heading here, creating tensors with, and then if we go backtick, tf.Variable. Wonderful. So let's see what type tf.Variable is here. We could jump straight into it, but we want to have some practice looking up the documentation. So TensorFlow tf.Variable. Now the first probably, I reckon at least 100 times you read something in the documentation, especially if you're new to TensorFlow, it probably won't make too much sense. But once you've had a fair bit of hands-on practice, you'll start to get used to it. So tf.Variable, look how many different parameters we have here, far out. Traditionally, like in practice, I don't really read all of these. I go down and I like to see things being used. So here we go, tf.Variable 1 dot, so that should be a float, yes, v a sign. What's that? Well, we could keep going through that, but let's get hands-on. Again, if you want more about something from TensorFlow, look it up in the documentation, come through these code examples, write them out for yourself, and just check what the inputs and outputs are of the code that you're writing. So let's go back, tf.Variable. How might we create the same tensor with tf.Variable as above? This is going to be, as you might have guessed by the name, a changeable tensor. What's that? tf.Variable 10.7. So remember up here, we created a vector of 10.10. Oh, I said 10.10, 10.7. There we go. That's what we want. 10.7. Now we're doing it here. And let's have a look at this one. Unchangeable tensor. tf.Constant. And then we want 10.7. Wonderful. We're going to write these out. We're going to visualize them. Unchangeable tensor. Did I type out the variable names correctly? Yes, I did. Wonderful. Okay, now we get some different outputs. So the first one here is our changeable tensor that we created with tf.Variable. So tf.Variable, wonderful, shape, okay, 2, dtype. In 32, we've seen that before, NumPy, okay. Now this is tf.Tensor, which is the unchangeable tensor that we created with tf.Constant. You see these are output in order here, so this one first, and then this one, which is exactly what we've seen above before. Shape 2, dtype equals int32, NumPy array is of that. Wonderful. What do you think might happen if we tried to change one of the elements in our changeable tensor? It's all right if you're not sure, but let's try change one of the elements in our changeable tensor. So changeable tensor 0, or let's try to index it first. What comes up is NumPy 10. So we've got the first value here, so the 0 index. So what if we wanted to set that? We want to make a tensor which is 7, 7. So we want to set that first number, 10, to be 7 also. What happens if we try to visualize it here? Okay, we get an error. Resource variable object does not support item assignment. Okay, what if we go back to this documentation? So tf.Variable, they've created one here, similar to how we've created ours, but they've only got one element, which is a scalar. Then they've used v.assign. All right, and then it's changed from 1 dot to 2 dots. So what if we tried that? So let's come back here. How about we try dot assign? All right, changeable tensor, and the 0th element dot assign, and then we want to change it to 7, just 7. What do you think will come out here? Let's have a look. Ooh, wonderful. There we go. All right. So how about if we tried to change a value in our tf.Constant tensor, or our unchangeable tensor? Now let's try change our unchangeable tensor. Let's just try to do the same change. Make it simple. Unchangeable tensor, 0th element. Well, first we'll index it as well, just to check. Same output here, NumPy 10. And what if we go equals 7? What happens there? Oh, object does not support item assignment. Okay, so similar error to what we got up here. Oh, that's okay. We know the fix. We can just go assign 7. Oh, get that bracket back up on there. And then we'll check out the unchangeable tensor. Oh, another attribute error. TensorFlow Python framework ops eager tensor. Object has no attribute assign. So what do you think's going on here? We've got a changeable tensor, which is a tf.Variable, and an unchangeable tensor. Where our tf.Variable is changeable using the assign attribute, whereas our unchangeable tensor, which kind of makes sense if it's name, doesn't change even when we use the assign. Now you might be wondering, why can we change some tensors and why can't we change others? Well, it comes down to behind the scenes, when we're writing neural network code, we might want some tensors for their values to be changed, whereas we might want some tensors for their values not to be changed. So there's a variable tensor and there's a constant tensor. Now, again, we're going to reiterate the fact that a lot of the times you won't have to make the decision between using a variable tensor or a constant tensor. The decision will be made for you behind the scenes when TensorFlow creates tensors for your neural networks. But we're going to get very hands-on with that. And so speaking of TensorFlow creating tensors for our neural networks, let's have a look in the next video, which is going to be creating random tensors. Woohoo! That's exciting. I'll see you then. So we've seen how to make tensors with tf.Constant and tf.Variable. Let's see how we might create random tensors. So actually, I'll make that a size 3 heading. And I just want you to I'll point out something here that I've added to the last little section of code that we run. This is going to be a trend throughout the course, is that if there's like a little tidbit that you should be aware of, I'm going to use this key emoji and add a little note there. So rarely in practice will you need to decide whether to use tf.Constant or tf.Variable to create tensors, as TensorFlow does this for you. However, if in doubt, use tf.Constant and change it later if you need. So that's a little tidbit going forward. So if you ever see the key emoji with something coming after it throughout this entire course, throughout any of the notebooks that you use and the GitHub and whatnot, That's just a little tidbit to take note of for later. But let's get hands-on creating random tensors. So random tensors are tensors of some arbitrary size which contain random numbers. You might be wondering, why on earth would I ever want to create a tensor? Where's an example of one of our tensors? Like this, filled with random numbers. And I have a great illustration to show you. So let's go to our keynote slide here. This is what neural networks use to initialize their weights, in other words, the patterns, that they're trying to learn in our data. So if we imagine this diagram here, we have our inputs. Say we had pictures of food that we're trying to classify into ramen or spaghetti. We might turn that into tensors. We'll see how to do this in a future project. So this is our numerical encoding of our images. Then we might pass that numerical encoding to the input layer of our neural network. Then our neural network might learn representations which are called patterns, features, or weights. Then output those representation outputs, and then we convert them into something that we can understand rather than just tensors. But where does a neural network get these representations from? Well, in the beginning, it's going to initialize itself. Initialize is another common word you'll hear in deep learning. Initialize just means start with. Initialize its weights or the patterns it knows with random weights or random tensors. So this would be a random tensor to begin with. And then, as it sees different examples of photos of ramen and spaghetti, it's going to update its representation outputs. In other words, start to tweak these random weights and patterns to better suit our data. If we go through again, we're going to repeat this cycle with more and more examples. So if we imagine the float here, we've got images, we numerically encode them, our neural network initializes itself with random weights, in other words, a random tensor, and then as we start to show it more examples of what photos of ramen and spaghetti look like, it starts to tweak these random weights to be better adjusted to the patterns that are in our images so that our representation outputs line up better with our desired labeled outputs. So maybe in the beginning it gets these images, these two here, wrong, but then as it keeps going, it starts to learn them and it starts to get them right like these two here. So let's go back. That's a brief overview of how a neural network learns, but that's the context of where you might use a random tensor. So how might we create a random tensor? So let's create two random but the same tensors. Now, before we even write any code, we go how to create random tensors with TensorFlow. TensorFlow.random.uniform. Wonderful. So we could go through that, or we could start to write the code. Seriously, when I don't know something, that is the type of search that I will put into Google and look up. As much as I'm trying to teach you TensorFlow itself, I'm trying to teach you how to search for answers to solve your own problems. Because at the end of the day, I can only show you so much. But let's create random one, which is going to be tf.random.generator.fromSeed42. What is a seed? So the set seed for reproducibility. So we'll see what the random seed means in a minute. If you've ever used NumPy, it's very similar to NumPy's random seed. So random1 equals random1.normal. I want you to guess if we put in the shape parameter here. So if we come here, go to this first one, random uniform, shape. We've got random normal, shape 3,2. What shape will our tensor be if we were to press Shift and Enter? tf tensor, shape 3,2. Now, we've used normal here, but this is uniform. What's the difference? So output random values from a uniform distribution. What is a uniform distribution? Here we go. Wolfram.com. A uniform distribution, sometimes also known as a rectangular distribution, is a distribution that has constant probability. Whoa. So oftentimes when I read stuff like this, it takes me a long time to grasp it. If you're the same, I want you to realize that that's not necessarily a problem. It's because in practice, when you're writing these random tensors, again, a lot of it is done behind the scenes for you. What I want you to get familiar with is writing as much code as possible, like we've done here, and then starting to see what the outputs of that code is. The more and more you do it, the more familiar you will get with it. So let's create another one. Maybe we'll come up here, random2 equals tf random generator from seed 42, random2 equals random2.normal shape equals 3, 2. You might be wondering, Daniel, you've just looked up uniform and you haven't done anything with it. So what is normal? Well, great question. So what is TensorFlow random normal? tf.random.normal. Outputs random values from a normal distribution. Okay, tf random normal shape. All right, what is a normal distribution? See how we're sort of just pulling the thread here? This is what I do with any problem that I'm working on. A function that represents the distribution of many random variables as a symmetric bell-shaped graph images. Okay, so that's the normal distribution. Again, you can look into this more if you want, but we're going to be practicing writing more random tensors. So are they equal? Random 1, random 2, and now we'll use this equality operator to compare the two. Random 1 equals random 2. Are these equal? Let's have a look. What do you think? Are they going to be equal? Oh, yes we do. We have random 1, remember these come out in order, and then random 2. And so they've come from a normal distribution. This equality operator is this last one here, which is saying that the top left element is matching this top left element, true. The top right is matching here and here, so that comes out true. And then we get the same for the rest of the array. Beautiful. So I want you to know that the random tensors here, although these appear pretty random, these numbers, they're actually pseudo-random numbers. So they appear as random, but they really aren't. That's because we've set the seed here. Setting the seed says something along the lines of, hey, TensorFlow, create me some random numbers, but flavor them with x, where x is the seed. So what do you think would happen if we changed the random seed to my favorite number, which is 7? I have a dog called 7. She's beautiful. What do you think will happen here? We get some slightly different random outputs, but they're still the same between random 1 and random 2. Okay, we've seen how to briefly create some random tensors, and I mean, if we go how to create random tensors with TensorFlow, there's going to be a whole bunch of more different ways. But if we had our random tensors, or if we had just non-random tensors, what if we wanted to shuffle the order that the variables appear in here? Let's have a look at that in the next video. In the last video, we checked out how we can create some random tensors, and we tied that back to the concept of when a neural network starts to learn, if it wants to learn patterns in some sort of data set, it starts off with random patterns and then slowly adjusts them as it continually learns on more and more examples. So if we come back here, in this video, let's see how we might shuffle the order of, what should we call it, elements in a tensor. All right. Why would you want to shuffle the order of elements in a tensor? Let's go back to our example here. So let's say we were working on a food image classification problem, and we had 15,000 images of ramen and spaghetti. Let's keep it nice and simple. And the first 10,000 images were all of ramen. And the last 5,000 images in our folder, like they're in order, so the first 10,000 are all of ramen, and the last 5,000 are all of spaghetti. Now, this order could affect how our neural network learns. So if it goes through these images in order, it might start to adjust its random weights too much so to the images of ramen, because if it goes through 10,000 images of ramen, it's like, okay, well, I only have to learn what ramen looks like. It doesn't know that it has to also learn what spaghetti looks like until it goes to the last 5,000 images. So instead, it might be a good idea to just mix up all the images in our folder so that they basically have no order at all. So we might have ramen, 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 spaghetti, spaghetti, ramen, spaghetti, ramen, spaghetti, ramen. And then the neural network can be fed different examples of different images and adjust its internal patterns or weights, the random tensors it got initialized with, to learn both types of images at the same time. Let's go back to our Colab notebook and let's see how we might shuffle a tensor. So we go shuffle a tensor. So this is valuable for when you want to shuffle your data so the inherent order doesn't affect learning. Now, what we might do is create another tensor. We'll get some practice creating tensors here. Not shuffled equals tf.Constant. And then we might just create a very similar tensor to what we created above, 10, 7, my favorite combination of numbers, my favorite poker hand. And there we go. And 2, 5. Why not? There we go. So a little test here is if we did not shuffled .ndim, what do you think that's going to output? Well, let's find out. 2. Okay. Why might that be? Not shuffled. Because it has a shape of 3, 2. So there's 2 elements in the shape attribute. Beautiful. So let's see how we'll shuffle this. Maybe if we just go how to shuffle a tensor in TensorFlow. tf.random.shuffle. Okay, beautiful. So randomly shuffles a tensor along its first dimension. tf random shuffle seed equals none value. Okay, there's an example output. Let's try it out. So the value, what's value? This is how I read the documentation. So the arguments. So the value is a tensor to be shuffled. That's what we want. And the seed could be a Python integer used to create a random seed for the distribution. C random.setSeed for behavior. Okay, let's get hands-on with this. So shuffle our non-shuffled tensor. So let's go tf.random.shuffle. And then, oh, look at that. The doc string appears for us. If we wanted that on our own, we could press Command-Shift-Space. See, I'll come, in Colab, it automatically, sometimes the doc string just automatically comes up if you're just chilling in here. But we can press Shift-Command-Space, or if you're on Windows, Shift-Control-Space. There we go. We just get the exact information from the TensorFlow documentation. How handy is that? So let's pass it. What does it take? Args, value, a tensor to be shuffled. Let's pass it in not shuffled. Okay. What do you think is going to happen here? Well, let's find out together. Boom. Okay, look at that order there. So if we get 10, 7, 3, 4, 2, 5, and now the order's changed up here. Okay, so there's still 2, 5, still 10, 7, still 3, 4. Okay, what it's done is if we come back up here, randomly shuffles a tensor along its first dimension. So if we look at not shuffled, it's got a dimension of 3 times 2, which is 1, 2, 3 elements. So it shuffled it along its first dimension, which means it shuffled it along this dimension here. So the 3, 1, 2, 3. So it means that the elements in the second dimension, which is 10, 7, 3, 4, 2, 5, have stayed in order, but they've been shuffled around. So 10, 7 was at the top, but now it's in the middle. 3, 4 was in the middle, but now it's at the bottom. And 2, 5 was at the bottom, but now it's at the top. Okay, Now, what if we were to run this cell again? I want you to take note. Actually, let's copy this. So copy that, and I'm going to add another code cell here. I'm going to run this cell here. Okay, 10, 7, 3, 4, 2, 5. Same as before, but what if we run it again? 10, 7, 2, 5, 3, 4. Okay, different order. Notice how every time I run it, it's a different order. And I mean, there's only 3 elements here, so sometimes you're going to get the same. Now, what if we were to put seed equals 42? Because if we come here, a Python integer, seed used to create random seed for the distribution. What happens if we do that? Seed equals 42. Seed equals 42. We get still different results. So what if we did tf.Random.set seed 42? Okay. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Okay. 10, 7, 3, 4, 2, 5. Now we're getting the same order. That's quite confusing. So how might we figure this out? If we come back here, seed, we set that to 42, but we didn't get the same results. So seed, it says here, used to create a random seed for the distribution C, TF random seed for behavior. Okay, so let's click on that. Here we're kind of pulling the thread of what our problem is. We're trying to figure out how to set random seeds or random operations in TensorFlow. So operations that rely on a random seed actually derive it from 2 seeds, the global and operation level seeds. So I think this one might be the global level seed, and this one might be the operation level seed because it's a part of an operation here. That's my intuition. Now, its interaction with operation level seeds is as follows. Okay, so we've got 4 rules here. I'm not going to read these out, but what I want to do is put this here, and I want you to start exploring or start practicing. So this is your homework for this lesson, so this one can be here. If you see this symbol here, this means exercise. So exercise, we're going to go read through TensorFlow documentation on random seed generation and practice writing 5 random tensors and shuffle them. That's your takeaway for your homework for this lesson. It's all right. If you want to skip over that and just go straight to the next video, you can. But to really understand the concept of TensorFlow creating tensors, just go through and try create maybe 5 different tensors here with tf.Constant. Then shuffle them. Then try to get the reproducible shuffled order using tf random set seed and a combination of seed. And then figure out just see what happens. If in doubt, run the code. You can't break it. So have a practice of that, and I'll see you in the next video. We'll see a few other ways to make tensors. In the last video, we went over the concept of shuffling the order of elements in our tensor. And we tried it out a few times, but we ran into some problems using the global random seed and the operation level random seed. But the main intuition behind shuffling the order of tensors is that if we were trying to build a food image classification neural network, and we had 15,000 images of food, 10,000 images of ramen, 5,000 images of spaghetti, and our neural network, all it saw was the ramen images first, the patterns that it learns may be too aligned with what's in a ramen image rather than a spaghetti image. So that's why we might want to shuffle the order of our images so that the patterns that our neural network learns are tuned to both kinds of images throughout the entire training cycle. So let's go back here. We also left off, last video was full on. We left off with an exercise to read through the TensorFlow documentation. Again, the first few times, or the first probably 100 times you read through the documentation, you might not fully understand it, but with a lot of practice, you'll start to get the concepts. And so what did you find? Did you try to create 5 random tensors and shuffle them? I'll tell you what I found. After reading these rules, number 4, I think, is what relates most to us. It says, if both the global and the operation seed are set, both seeds are used in conjunction to determine the random sequence. Okay, so if we come back here, if we set tf.Random.Shuffle, we try to shuffle our, so this is the operation level seed. So if we run that, okay, we get a different order each time. But then, if we set the global random seed, what do you think is going to happen? So we'll go here, global level random seed, operation level random seed. Do we get the same order every time? 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. 10, 7, 3, 4, 2, 5. Beautiful. We could keep going, but we're just going to trust that this rule is correct. So here, we come here. Let's write down here. It looks like if we want our tensors, or maybe our shuffled tensors, that's a better way of saying it, our shuffled tensors to be in the same order, we've got to use the global level random seed as well as the operation level random seed. And then we'll put in here, if you want to put in a quote, you can do this little arrow thing here. Rule 4, there we go. So again, now this might not make a lot of sense of why you want reproducible tensors, but as you start to run more deep learning experiments, you'll often find is that because a neural network initializes itself with random patterns, you could get different results every single time you run this experiment. So, to make reproducible experiments, you probably want to shuffle your data in a similar order, initialize with a similar random pattern, and then run through this experiment. But for now, just be aware that if you want to set the random seed, TensorFlow has a few rules that you have to adhere to in order to get reproducible randomness. Whoa, that's a bit of a tongue twister. So let's have a look at some other ways to make tensors. Other ways to make tensors. The first one is if you're familiar with NumPy, you can do NumPy 1s. What's this? NumPy 1s. Let's have a read. Return a new array of given shape and type filled with 1s. So for many NumPy operations, because NumPy is one of the most prevalent numerical computing libraries out there, TensorFlow has similar operations. So TensorFlow 1s creates a tensor with all elements set to 1. Okay, let's try that out. So tf 1s, what happens here? Let's check the doc string. Can we do that? Yeah, there we go. tf 1s, it looks like we have to pass it a shape and then a data type. So why don't we make it 10, 7? What happens? Wonderful. Create a tensor of all 1s. And then we want to go maybe create a tensor of all 0s. Oh, how do you think we might do that? If we created a tensor of all 1s, how might we create a tensor of all 0s? I wanted you to try and guess this before we even bother looking it up. Let's go tf 0s. And then what shape should we pass this under? So this is in square brackets. Shape you can also pass in curly brackets here, or the curved brackets. How you'd create a tuple. 3, 4, put a space there. Wonderful. Okay, so if we wanted to create a tensor of all 1s and all 0s, we can do that using tf1s or tf0s, very similar to NumPy. And another thing, speaking of NumPy, we might as well cover that while we're here. You can also turn NumPy arrays into tensors. Whoa, into TensorFlow tensors. So remember, the main difference between, well, actually, I don't think we've covered this, but actually, let's put this here. We want text, so I'm going to push Command-M. We'll go here, turn NumPy arrays into tensors. And the main difference between NumPy and TensorFlow, this should be NumPy arrays, is that tensors can be run on a GPU much faster for numerical computing. Otherwise, they're very similar. So let's try this out. We want to import NumPy as NP, and then we want to create NumPy A. This capitalization, often you'll see a matrix created with a capital, constant, sum matrix, and then often you'll see a vector with a non-capital. So that's a little tidbit there too. So we'll put that there. And then we'll go little capital for matrix or tensor, non-capital for vector. So we want to make just a simple NumPy array. Range, dtype is going to be int. Actually, we'll make it int32. So this is going to create, you might be able to guess, so NumPy A range between 1 and 25. So create a NumPy array between 1 and 25. Let's have a look at that. NumPy A. Now, how do you think you might turn this into a tensor? So if we come back to our tf.Constant documentation, creates a constant tensor from a tensor-like object, value. Okay, what's value? Where's the doc string for that? Value. A constant value or list of output type dtype. It doesn't really give us much, but let's try. If in doubt, code it out. A equals tf.Constant. Do you think we can just pass our NumPy A, this one here, directly to tf.Constant? I mean, what do you think is going to happen if we do this? Oh, wonderful. There we go. We've now just converted our NumPy array. So if we have a look here, the output here is an array that's of type NumPy. And then if we go here, we've just passed it to tf.Constant. Now it's into the form of a tensor. How beautiful is that? So anything we've got in NumPy, we can convert to a tensor by just passing it to something like tf.Constant. Now, what if we wanted to change the shape of this? So this is a shape 24. How about if we wanted to make it into a 3-dimensional tensor? Yeah, that sounds fun. So let's change it into 2, 3, 4. Is that the right? 2 times 3 times 4. Now, why do you think I checked that? We'll see in a second. Hey, look at that. Maybe we'll make this b equals tf.Constant NumPy A. And then we'll go A, B. Ooh, so there's a change shape one. Our first one, A. We've got the shape modifier there. So this is 1, 2. So 2 is the first dimension. And then 3, 1, 2, 3. And then 4, 1, 2, 3, 4. Wonderful. But the unmodified shape is just the same shape as our original NumPy array, which is just 24. So this is a vector, and this would be a tensor because it's got more than one dimension. Now, the important thing to know about shape is that if you want to readjust the shape of a tensor or an array, the new elements here must add up to give the same number of elements in the original tensor. So what if we tried here? What's going to happen? It doesn't work. Eager execution of tf constants with unsupported shape. Value has 24 elements. Shape is 2, 3, 5 with 30 elements. So if we go here, that doesn't work. We go there. Wonderful. We need it to equal 24. So what about 3 times 8? Let's try that. 3 times 8. We're kind of getting a little bit ahead of ourselves here with this reshape. Oh, look at that. Beautiful. So 3 times 8 equals 24, so that works. So this is 1, 2, 3 rows, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 elements per row. Beautiful. Okay, So we've seen how we can turn NumPy arrays into tensors, and we've seen how to create tensors with all ones and all zeros. It's probably time that we get a little bit more information from our tensors. So let's make that in our next video. So getting information from tensors. All right, so have a play around, create some NumPy arrays, turn them into TensorFlow tensors, and then try to adjust their shape so they fit into a different size. And then you could even check the number of dimensions of A. But otherwise, give that a go, and I'll see you in the next video. We'll see how we can get more information from our tensors. We finished up the last video checking out how NumPy arrays, which are a very common form of representing numerical data, can be used or actually also converted into tensors. And the main difference being between a NumPy array and a TensorFlow tensor is that although they may store the same information here, so this array here, NumPy A, has the numbers 1 to 24, and this tensor here, B, has the numbers 1 to 24, is that because this one's in a tensor format, it can run on a GPU, which we'll see later on in the course is a lot faster than a non-GPU chip at finding patterns in numerical data, that is. Let's have a look at how we'll get a bit more information from our tensors. But before we do that, I just want to show you a little tidbit. So I took a break after this lecture and came back to my notebook. And what happened was the runtime disconnected. Now you can't see it here, but we've got a green tick saying we're connected. But when you disconnect in Colab, you might find that, oh, it's still there. But if the memory has gone, so for example, if we did A and it told us that A didn't exist, what I like to use is go to runtime and then run before. What this is going to do is run every cell before the current cell, meaning if we've instantiated some variables such as NumPy A, those variables are going to get reinstantiated and TensorFlow is going to get re-imported, etc. We don't necessarily need to do it now because, or in my case, because it seems that Colab has remembered my variables. But if you do come into that case, go runtime, run before, and as you'll see, all the cells here are going to run. Now they run pretty quickly. We get the same error we got before, but then we can just go Shift Enter, run, keep running down to where we were. And then all of the variables we've been working with will be reinstantiated. Wonderful. So with that being said, let's get back to our getting information from tensors. There will be times where you want to get different attributes of your tensors. Let's have a look. Let's have the following vocabulary at least. So we want shape. These are the most important tensor terms. Axis or dimension. And then you'll also want the size. So if we come here to our keynote, we'll have a look at how to do those in code in a minute. But if we go on to the next slide, these are some of the main tensor attributes here. So we've got shape, axis or dimension, and then size. And the meaning here, the shape is the length or the number of elements of each dimension of a tensor. And we can get that by going tensor.shape. The rank, the number of tensor dimensions. For example, a scalar has rank 0 or 0 dimensions. A vector has rank 1 or 1 dimension. And a tensor has rank n or n dimensions, where n can be almost any number, 0 and above. And then we can get that by going tensor.ndim. We've seen that a few times. Axis or dimension. So this is how you access a particular dimension of a tensor. For example, if we wanted to index on the first dimension, tensors are 0 index, so the first dimension is actually 0, 1, etc. And then if we wanted to get all of the elements in the 0th dimension and then the 1 axis, we can use some indexing like this. We'll see this in a minute. And then if we wanted the size attribute, the size is the total number of items or elements in a tensor. And we can access that by using tf.size. So let's go back. When dealing with tensors, you probably want to be aware of the following attributes. Boom. Shape, axis, rank, size. I said that out of order, but that doesn't really matter. So probably the most important one here will be shape, but we'll see that again in practice. Let's create a tensor. Create a rank 4 tensor. Now, if I say rank 4 tensor, if we come back here, what does that mean? Rank, the number of tensor dimensions. So what might that look like? We want 4 dimensions. We come in here, we want rank 4 tensor equals tf.zeros. What does tf.zeros do? This is a little test from before. We just covered this one. 2, 3, 4, 5. So remember, this is probably the shape parameter here. So rank 4, we've got 1, 2, 3, 4 dimensions here. Now let's have a look at this rank 4 tensor. Beautiful. Now this is all zeros. So if we see here, this is 1. So this is the first axis. This is 1, 2. Then the next one is 3. So we've got within the 1 and 2, we've got 1, 2, 3. Now this will take some getting used to. The only reason I'm able to sort of deduce which is which of these elements here is because I've had a lot of practice writing different tensors. Now if we look at 4, within the 3, so 1, 2, 3, we've got 1, 2, 3, 4. And now we've got 5. So within the 4, 1, 2, 3, 4, we've got 1, 2, 3, 4, 5. Now, as we'll see later on, I know I keep saying later on, we're getting the fundamentals down pat here, is you'll probably spend most of your time dealing with lining your shapes of your tensors up. When you pass a tensor into a neural network, it typically has to be in a certain shape, and then the output tensor that comes out of a neural network, so in other words, the patterns a neural network has learned, the tensor again has to be in a certain shape. So it's good to be able to deduce different elements of a tensor by its shape. So if we wanted rank 4 tensor, let's get its 0th element. What does that look like? Which is this 3 tensor here. So see how we've indexed onto this second shape here? Now the shape changes because we're getting this set of 3 here, this set of 3 tensors. And so the shape here is 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Again, it'll take quite a bit of practice to get used to that, but that's just a brief overview. Now, what we might do is get all of the shape, the rank, axis or dimension, and the size of our tensor. So we just saw the 0th axis. Let's go rank 4 tensor dot shape. You might be able to guess what this is already. Rank 4 tensor dot ndim, so the number of dimensions. And then let's get the size of our tensor. Before I even type any of these, you might be able to deduce what they actually are already. So what's the shape? Probably going to be similar to what we set the shape as. The ndim, remember that's the number of dimensions in our tensor. And the size is what, if we come back to our keynote? The size is the total number of items in the tensor. Out of all of these, I think size will probably be the one you use least often, but I'm just putting it here for completeness. So if we go there, boom. So we look, these come in order again. So the shape is 2, 3, 4, 5, yep. The number of dimensions is 4, that makes sense because it's 1, 2, 3, 4, beautiful. And then the size is there's 120 elements. Now, what might that be? I'll give you a hint. 2 times 3 times 4 times 5, what do you think this is going to equal? 120. Beautiful. Okay, how about we print out some various attributes of our tensor, make them a bit more readable. So I want to show you, get various attributes of our tensor. This is what I often do to sort of create I call this pretty print statements. I mean, there is a function called pretty print, but when I'm trying to figure out or visualize my tensor data, I typically set up a bunch of print statements like this, especially when I'm inspecting the outputs of a neural network. So print, so I want to get the data type of every element. Boom, that's what I want. And then I want to get the number of dimensions, which can be the rank. And again, typing this stuff out is tedious when you first do it, but it does help visualize. I mean, we could put this into a function if we wanted to later on. Print, and now how about the shape of our tensor? that's going to be rank 4 tensor.shape. I'm not sure why that disappeared. Beautiful. And then now, how many elements are along the 0th axis? So elements along the 0 axis. Oh, axis doesn't have that. And we want to go rank 4 tensor 0 dot shape. Oh no, maybe we want shape 0. That's what we want. And then how about we want elements along the last axis. So I want rank 4 tensor shape. Now -1 we can use for the last axis. So instead of we have 1, 2, 3, 4 here, we could have used 3 because it's the 4th index, but we're going to use -1 just to grab the last index. That's a little trick for Python indexing. And then we want to go the total number of elements in our tensor, which will be tf size rank 4. Is this going to autocomplete? Rank 4 tensor. That should be ready to go. Let's have a look. What do we get? Okay, data type of every element. Dtype is a float. So, okay, that makes sense because we've got 0 dot. Yep. Number of dimensions, rank 4. Yes, that makes sense. 1, 2, 3, 4. Shape of tensor. Yes, we've seen that before. Elements along 0 axis. So 2 elements there. Yeah, beautiful. Elements along the last axis. 5. That's correct. Wonderful. And the total number of elements in our tensor is tf tensor 120. Oh, NumPy 120. Now that output can be a little confusing, so I want to show you just a trick to convert it into a NumPy integer. So you can just go here. With the tensor output, for a lot of them, you can just add .numpy on the end, and we'll watch the conversion here. So this is there, or actually we might do it with and without, just so you can see the difference. I'm just going to copy that line. Boom. There we go. So the total number of elements in our tensor, that's it coming out as a TF tensor type. But if we add the NumPy on the end, we get it in this single element, which can be handy if you didn't want to have the TF tensor type. You just want the element itself. Try using .numpy at the end there. All right, wonderful. Since we now know a fair few pieces of information on how to get them from our tensors, we'll practice. One very important thing is being able to index on tensors. So we'll do a little bit of practice of that in the next video. So I'll see you then. So in the last video, we checked out how we can get various attributes from any tensor that we can create, such as the data type, the number of dimensions, the shape, and then various other attributes of it, which can be helpful when we're trying to figure out just what's going on with our tensors. Because, I mean, although we can see this one, oftentimes with neural networks, you'll be dealing with tensors that you can't actually visualize, meaning that they're so big that you won't be able to just look at them. So you need to be able to use code to find different information or different attributes about them. So now let's have a look. Say we did have a tensor like this, and we want to index it. So the beautiful thing about tensors is that, oh, we don't want that. I just want to turn that into text. So we'll go here, indexing tensors. So tensors can be indexed just like Python lists. So if you've ever done indexing on Python lists, we'll see how it relates here. But if not, that's okay, because we're just going to get hands-on as we do. That's the theme of this course. So get the first 2 elements of each dimension in our tensor. So if you have had experience with indexing Python lists, how do you think you might get the first 2 elements of each dimension of our rank 4 tensor? So remember, we've got 1, 2, 3, 4 dimensions here, and we want the first 2 elements. In our case, it's going to be 0 for every single one of them, but we want the first 2 elements of each dimension. So give that a try. If not, I'm going to start writing the code to do it, and we're going to have a look at it in a few seconds. So this is how I would get, or how you would index a tensor to get the first 2 elements of each dimension. There we go. So just like a Python list. So if we make here sum list equals 1, 2, 3, 4, and we want the first 2 elements of sum list, we go here. Use a colon, we'll get 1, 2. Beautiful. So now we can do the same, but with our tensor. We just have multiple dimensions. We separate them by column. So let's have a look at what the output of this is. Wonderful. Because our tensor is all zeros, we get 2, 2, 2, 2, and each value is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. But can you see the shape here? This is the first, the outer tensor. This is the second one on the 0th dimension. And then we have 2 here, 1, 2. And then we have 2 within these brackets, so 1, 2. And then the final 2, the elements within the most inner brackets, so 0, 0. Again, takes a lot of practice, but just look at these diagrams and start to count the tensors yourself of tensors that you can visualize. As a warning, if the tensors are too large, it'll probably separate them with 3 dots, but we'll get to that in a bit. How about if we wanted to get the dimension or get each dimension from each index except for the final one? Now, does that make sense? So we want get each dimension from each index except for the final one. Oh, sorry, that doesn't make sense. Get the first element from each dimension, from each index except for the final one. Okay, how might we do that? Actually, let's try it with our sum list. If we wanted the first element, 1. Beautiful. Now, we want the first element from every dimension except for the final one. So let's try that. Rank for tensor, and we want first element from each dimension except for the last one. Will that work? We don't have the last one there. Let's try. Wonderful. 1, 1, 1, 5. Beautiful. So that means all of our tensors kind of get flattened. All the other shapes get flattened into 1, but we've still got 5. Beautiful. We can get the same thing if we add this colon here. So this colon, if it's there without a number, it just means get the whole thing. So there we go, same output as before, 1, 1, 1, 5 for the last dimension. Now if we wanted to change this up, say we wanted the, except for the second last one, what do you think this is going to output? If we go here, rank for tensor, if we want to get the second last axis, and we go shape. So we're getting the first element from each dimension of our tensor except for the second last one. So what shape is this going to output if we run this line? Let's try. Wonderful. So there we go. 1, 1, 4, 1. Again, plenty of practice, but that's how we're going to learn things. So there we go. 1, 3, 1, 1. Then we could do the same here with the 0th axis. Beautiful. Okay, we'll convert that back so that comment there makes sense. Now, what else might we want to do? If we've got our tensor of this shape, sometimes what we might want to do is expand or reshape. So in this case, we've seen a little bit before on how to reshape a tensor, but let's practice changing or adding an extra dimension to the end of a tensor. So how about we create a rank 2 tensor, which has how many dimensions? 2 dimensions. So we can do that by rank 2 tensor. You can pause the video here if you want and try to create your own rank 2 tensor without me coding. But we want tf.Constant, my favorite numbers, 10, 7. And then how about 3, 4, because 3 and 4 add to 7. And now let's have a look at our tensor. Rank 2 tensor. We could even get some attributes about it. Rank 2 tensor, ndim. Again, lots of practice here, figuring out information about our tensors. Okay, the shape 2, yep, ndim, that's exactly what we want. Now, if we wanted to get the last item of each row of our rank 2 tensor, how might we do that? So again, let's remind ourselves what it looks like. Rank 2 tensor. Let's remind ourselves what our Python list looks like, sum list. How do we get the last element of a list? Sum list -1. So there we go. So if we want to get the last item of each row of our rank 2 tensor, well, the row comes first, so row, column. So we might go Rank 2 tensor. So the last item, -1. Does that make sense? Let's see. Does that get it? So 7, 4. Beautiful. That's what we want. If we wanted to add an extra dimension onto this shape here, so maybe we have 2, 2, 1, we can do so in two ways. And now this is helpful for later on when we're creating neural networks and we need to alter the size of our tensors so that their shapes line up. So it might not seem like it's very helpful now, but I just want to sort of plant the seed so that when we come across it in future videos, it's not like, whoa, Daniel, we haven't covered this method before. So let's go in here, add in extra dimension to our rank 2 tensor. So we want to turn our rank 2 tensor into a rank 3 tensor, but keeping the exact same information that is stored in our rank 2 tensor. So we're not going to change these numbers. We're just going to change the shape that the numbers fit into. And we can do that by going here, ... Now this is a little bit of fancy notation. You might not have seen this before. We can go tf.NewAxis. Let's see what this does. Oh, we need to visualize our tensor, don't we? Beautiful. So you see what that did there? That's now added a dimension on the end of 1. So let's look this up, tf.NewAxis. tf tensor. If we search, again, I'm just pressing Command F, you might press Control F, tf.NewAxis. There we go. So 1 of 8, it appears 8 times. So insert another dimension. Does it have the actual definition here? Notes tf.NewAxis is none as in NumPy. So if you're using NumPy, you probably use none. In TensorFlow, it's tf.NewAxis. It doesn't actually say what it does. Sometimes where you'll find the documentation, it can be quite hard to sometimes find the exact definition of this method, but you can kind of deduce what it does by running through the examples as we see here. So let's go in there. It's better off just to remember, if in doubt, write the code, try it out. So the other alternative to using this, oh, by the way, these 3 dots means on every previous access to this one. So this means instead of just going like this, so see how we've got access 0, access 1, access 2 in this case, add an access on the very end. We can just scrap these and go every access before the last one, include those because that's ... and add a new access on the end. So the other alternative to tf.NewAxis is alternative to tf.NewAxis. You might also see tf.expandDims. So that stands for expand dimensions. And then we're going to pass it rank 2 tensor. And then we want to expand it on the final axis. So -1 means expand the final axis. There we go. We get the exact same output as this notation here. It's just slightly different. So if we want to go here, tf.expandDims. There we go. We got some documentation for this one. So we have the input. We come down. It says, what is the input? The input is a tensor, and the axis is integer, specifying the dimension index at which to expand the shape of input, giving an input of d dimensions. So if we come back here, what do you think will happen if we go axis equals 0? So look at our shape there. What I might do is keep that there. We're going to retype this out. tf expand dims rank 2 tensor. We want as much practice as writing TensorFlow code as possible, right? So expand the 0 axis. So let's try that. Boom. So now, instead of being on the end, our extra dimension is at the front. And then we can even change it. We want the extra dimension in the middle. Wonderful. And then if we want to put it on the end, we can go -1. Beautiful. So we might put that there. Expand the 0 axis. And so notice, even if we run this and we check out rank 2 tensor, the numbers inside stay the same, 10, 7, 3, 4, except the dimensions change. So how those numbers are stored changes. We've covered a fair bit in terms of getting information from our tensors and also indexing our tensors. Now, let's have a look at how we might. We've actually done a little bit of manipulation here too, but the next videos, we might go through manipulating tensors. In other words, known as tensor operations. So if we do have elements within our tensors, how do we manipulate those and how do we combine them into different ways? So go back through, practice expanding the dimensions of tensors, practice getting different attributes from tensors that you've created. And then in the next video, we'll see what kind of tensor operations we can work with. If your data is stored in some sort of tensor format, finding patterns in those tensor formats often involves manipulating tensors. Now, again, when building models in TensorFlow, much of the pattern discovery within tensors is done for you. However, oftentimes that pattern discovery is through the extended use of a few basic operations. So let's start getting into those, otherwise known as tensor operations. We'll start off with basic operations. Now, do we have a tensor? So you can add values to a tensor using the addition operator. And by the way, when I say basic operations, I'm talking about the default Python operators such as plus, minus, multiplication, and then if we want divide, we can go like that. All right, so we can add values to a tensor using the addition operator. So let's create a tensor equals tf.Constant, and we might make it 10.7, my favorite, and 3.4. And now if we go here, plus 10, what do you think will happen? So this is our tensor here. And if we just use the basic operation of tensor plus 10, wonderful. We get 10 plus 10 is 20, 7 plus 10 is 17, 3 plus 10 is 13, and 4 plus 10 is 14. Wonderful. Now you'll notice that the original tensor is unchanged. This is important because when we're manipulating tensors, we don't necessarily always want to change the underlying tensor. The only way it'll change is if we go tensor equals tensor plus 10. We'll reset it. Now this is going to be plus 20, isn't it? There we go. We'll come back here. And there we go, tensor. But if we got rid of this, tensor, we rerun this cell. Oh, invalid syntax. And then we rerun this one. We still get the same values as what our original tensor was. And we might just press enter there so it's more succinct with how it comes out. Beautiful. So, of course, other operations also work. So multiplication also works. So if we wanted to go tensor times 10, same thing. We get 100 because 10 times 10, 100, 70, 30, 40, etc. And then subtraction if you want. So tensor minus 10 can go into the negatives. That's no problem. Tensors can store a whole range of different values. In addition to the operators, like the Python operators, we can also use an equivalent TensorFlow function. Now, what this means is that if we do use the TensorFlow function, so that means we're accessing the TensorFlow library. Let me just show you, because it's easier to talk about something if we can see it. We can use the TensorFlow built-in function too. So tf.multiply, and we want, see here, we get the doc string here. We get tf.mat.multiply, so we'll have a look at that in a moment, but I just want to demonstrate it to you. Tensor 10. We get the same output here. So if we go here, let's look up tf.math.multiply. So for a lot of these tf.math functions, so tf.math, we can do the alias of just tf multiply. So if we go tf multiply, it's just going to lead us to the same thing. Wonderful. Now, does it say here what the benefits are? It doesn't quite. But what I'm going to get you to do is just trust me here when I say that if you have to do some sort of tensor operation like this, and again, Usually a lot of these will be done behind the scenes for you. But if you want your code to be sped up on a GPU, typically it gets sped up when you use the TensorFlow version of some sort of operator. So if we wanted to do addition, I mean, this is going to be very fast because it's only a small tensor. And we could do tensor plus 10. But if you want to have the advantages of TensorFlow built into your basic operations, use the tf math something tensor to manipulate your tensors. But here, again, even though we've used the TensorFlow function here, the original tensor is still unchanged. So these are the basic operators. Create some tensors, have some practice at running the addition, minus, multiplication, and division on them, and also do the equivalence of tf.multiply or tf.addition or something like that. Is it tf.addition? tf math addition? Or is it just add? Yeah, add. Okay. That's your little homework for this brief video here. But in the next one, we're going to have a look at a very important concept in neural networks, and that is matrix multiplication. We'll see how to do that with tensors. So we left off in the last video figuring out how we can manipulate our tensors with the basic operations. And so hopefully you've tried out a few of these for yourself. But now we're going to go on to matrix multiplication. So in machine learning, matrix multiplication is one of the most common tensor operations. So the ones we've been through already, these basic operations, are often referred to as element-wise operations. So that means that if we go here, for the addition, for example, we've got our tensor here, which is 10, 7, 3, 4. Now, element-wise means go through one element at a time and just add 10. So this element, add 10. This element, add 10. This element, add 10. This element, add 10. But there's a few different types. So matrix multiplication and the dot product are not necessarily element-wise. So if we go here, what is matrix multiplication? How to multiply matrices. Math is fun. I really like this domain name, actually. Let's have a look here. A matrix is an array of numbers. To multiply a matrix by a single number is easy. So 2 times 4 equals 8. Yes, that's what we've done, right? So that's element-wise. So 2 times 0 equals 0, 2 times 1 equals 2, 2 times -9 equals -18. Beautiful. However, what if we wanted to multiply a matrix by another matrix? And remember, because we're using TensorFlow, even though this is a matrix, we're referring to them as tensors as well. So I want you to read this as matrix and tensor interchangeable. But to multiply a matrix by another matrix, we need to do the dot product of rows and columns. What does that mean? Let's see an example. So the dot product is the first row and the first column. Okay, so we've got a row here times this column equals 58. Okay. The dot product is where we multiply matching members, then sum them up. So 1, 2, 3 times 7, 9, 11. Okay, 1, 2, 3 times 7, 9, 11, yes. Equals 1 times 7. Okay, yep. 2 times 9. Yeah, 2 times 9. 3 times 11. Okay, I've got that. That equals 58. Then we do it again for the second column, and that's 64. And then again. A great website I like to visualize this is, I believe, matrix multiplication.xyz. We'll go to that. So here, beautiful. We can even customize these. So we'll go here, 1, 2, 7, my favorite number, 7, 2, 1, just to be fancy. And then maybe 3, 3, 3, because I like 3 as well. And then this can just stay the same. So might zoom in here. So let's go multiply. What happens? Whoa, we get some. So that tensor just came up there and jumped on top of that. And then if we go through, we go 1 times 2, 2 times 6, 7 times 1. Okay, so that's 2 plus 12 plus 7. How did this get to 21? 2 plus 12 plus 7. We might try a different set of numbers. How did that work? 5. Maybe our matrix multiplication demo is busted. Multiply. Let's try. 1 times 3 plus 12 plus 5. Does that make sense? So 3, 12 plus 5. Yeah, that makes sense. 15. So this is 3 plus 12 is 15 plus 5 is 20. There we go. And if we step through there, step through, wow, we get the output there. Before we even start to write code, go to this website, start practicing around, see what happens. And after you've done that for about a minute or so, or maybe 3 minutes, give yourself a few different goes. Let's go back to the notebook and see how we can do this exact operation in TensorFlow code. So I'll give yourself a second there, but I'm going to start coding so you can pause the video now if you want, try out that website and come back. So let's see matrix multiplication in TensorFlow. What if we just Google that, matrix multiplication in TensorFlow? MatMul, there we go. tf.linalg, which is short for linear algebra, .matmul. Multiplies matrix A by matrix B, producing A times B. A, B. And we get a whole bunch of documentation, which is beautiful. We could read through that, or we could write the code ourselves. So, what do we have? Do we have a tensor? Print our tensor. We can print it if we want. Print, yes we do. Now tf matmul. Now for a lot of these operations, you can usually drop the intermediary here. So linalg, this is a little trick of TensorFlow. You can just do tf.matmul, which is what I'm about to do here. tf matmul, tensor. Can we matrix multiply those? Oh, yes we can. Wonderful. We get 121, 98, 42, 37. Beautiful. Now, if you wanted to do the matrix multiplication, Python has an operator, A. Now you see how the outputs here actually are different to if we just did, what if we did tensor times tensor? We get different outputs here. Okay. Because if we have a look at our tensor again, this is element-wise. So it's just gone 10, maybe we'll print it out twice. 10 times 10 is 100, 7 times 7 is 49, 3 times 3 is 9, 4 times 4 is 16. Whereas with MatMul, we've gone in this fancy little way here. So maybe, I've got an idea, we recreate this tensor. That could be a little exercise for you as well, is to recreate this tensor in TensorFlow and recreate this tensor in TensorFlow. So the same elements in the same shape. This would be a what? 1, 2, 3, a 3 by 3 tensor. And this would be a 1, 2, 3 by 2 tensor, so 3 by 2. And then run tf.matmul on left tensor, right tensor. See if you get the same outputs as here. But we come back here. If you wanted to do matrix multiplication with a Python operator, we can do tensor at tensor. So the at symbol in Python actually is for matrix multiplication. Now, both of these examples work because our tensor variable, this is an important fact. This is where we come in and we check the shapes attribute. Because our tensor.shape attribute is 2 and 2. So both of them have the same shape of 2 and 2. But what if we wanted to do matrix multiplication on tensors which had differing shapes? Now, rather than just think about it, let's try. So create a tensor of maybe 3, 2. Similar to this one here. So this is 3, 2. Remember, rows come first. 1, 2, 3. Columns, 1, 2. Let's create a similar one. Create a 3, 2 tensor equals tf.constant. And we want 1, 2. We'll keep this one nice and simple. 3, 4, 5, 6. Beautiful. And then we want create another 3-2 tensor. And in this case, it can be y, tf.Constant, and we'll just increase this one. So that can go from 7, 8, 9, 10, 11, 12. Wonderful. Let's have a look at both of those. X, Y. Okay, so we've got two tensors here, both of the same shape, 3 by 2, and they got slightly differing elements. Now, what if we tried to matrix multiply them? So let's try to matrix multiply tensors of same shape. We could do it like that. See what happens? Oh, matrix size incompatible. In 3, 2, in 3, 2. What if we try the TF MatMul? What happens here? X, Y. Invalid. Matrix size incompatible. Same thing. 3, 2, in 0. So this is our first element here, our 0th element. And this is our other element here, our first element, which is also 3, 2. This is where we have two rules for matrix multiplication. Do these websites tell us? Why do we do it this way? Actually, this is a great example. I'm going to put this as an external resource if we come back. If you ever see this emoji in the course, this is a resource. So resource, info, and example of matrix multiplication. So check that out. If you ever see that little book emoji, that's an external resource that I definitely recommend. Now, let's go back to here. Why doesn't this work? I don't think this web page explicitly states it, but I'm going to tell you anyway. You can look this up. You'll find this wherever you find matrix multiplication, is that there is a couple of rules that our tensors or matrices need to fulfill. So come up here. Let's put in here. There are two rules our tensors or matrices need to fulfill if we're going to matrix multiply them. Now, rule 1, the inner dimensions must match. And rule 2, the resulting matrix has the shape of the inner dimensions. So knowing these two rules, I'm going to set you a challenge. Is before the next video, we're going to go through these two rules and see how we can fix our problem here. But considering these two tensors, so we've got, if I say rule 1 is that the inner dimensions must match, what are the inner dimensions here? Maybe 2 and 3, they don't really match. So how would we get this, the inner dimensions of these two matrices to match? That's your challenge. If you're not sure, that's completely fine, but that's your challenge before the next video. If you can get it done, amazing work. If not, we're going to go through that in the next video. So I'll see you there. In the last video, we kind of left off on an error. And we said in this video that we're going to fix it. So let's do that. Now we tried to matrix multiply two tensors of the same shape, specifically x and y. They're both of the shape 3, 2. And we've got this little error here saying in 0 is 3, 2 and in 1 is 3, 2. So matrix size incompatible. So if we come up here, back to the rules we set ourselves, the inner dimensions must match. And the resulting matrix has the same shape of the inner dimensions. Now, if you had a go at fixing this and you got through it, excellent work. You may want to skip over this lecture. However, if you didn't make it, that's completely fine. Matrix multiplication takes a little while to get your head around. If we come over here, I've got a slide. Matrix multiplication is also known as the dot product. So when we call the code tf.MatMul, and we have a matrix of some size here and a matrix of some size here, remember, a lot of the operations that we do can be on matrices or tensors of an arbitrary size, but just for illustration purposes, I've done this size here. So here's our first rule. So numbers on the inside must match. And there's our second rule. New size is the same as outside numbers. Okay. So if we come back, does that line up with what we've said here? The inner dimensions must match. The resulting matrix has the same shape of the inner dimensions. Oh no. of the outer dimensions. There we go. Getting our own rules incorrect. So we come back. Let's have a look at what's going on here. We've got tf MatMul. We've got one matrix or tensor here, A, B, C, D, E, F, G, H, I, which is the shape of 3 by 3. Wonderful. And this will run because the numbers on the inside match. See these two 3s here with the red background? And this is of shape 3, 2. So 1, 2, 3, and 2 columns. Okay, so that matches. And then we're going to result in here. If we did the dot product, which is the same as matrix multiply in TensorFlow, we have A times J plus B times L plus C times N, and then we follow through with that rule for every single cell in these two, or every single element in these two tensors. And now the new size is 3 by 2. 1 row, 2 row, 3 row, 2 columns, which is the blue numbers here. Okay, wonderful. And then if we swap these elements from letters to actual numbers, so the same shapes here, we take 5 times 4. Okay, this is the same as A times J, yes. 0 times 6. Okay, 0 times 6, yes, which is the same as B times L. Wonderful. And then we have 3 times 8, which is the same as C times N. All right, now, again, looking at these diagrams, they're quite, for the first, I would say, 20, 30, 50 times you look at dot products and matrix multiplications, it takes a lot of repetition to get used to. But then if we have 5 times 4 equals 20, plus 0 times 6 equals 0, plus 3 times 8 equals 24. So we add these 3 up, we get 44 in the top left. Repeat the same for each element, and we get this resulting matrix here. Now, the live demo we've already had a look at. Matrix multiplication.xyz. This is what's happening here. If we reset and multiply, we take that, we flip it on the top, then we go here, we get 20, and we get the next 2 elements, and the next 2, and the next one. So this is a moving diagram of what's going on here. So let's go back to our code. Let's fix it up. Let's make it work. So knowing our 2 rules, number 1, that the inner dimensions must match, and that the resulting matrix is the same shape as the outer dimensions, how might we get this to work? Well, we're either going to have to change the shape of this matrix or change the shape of this matrix. Again, I'm using the term matrix and tensor interchangeably here. Or we're going to just have to create an entirely new tensor with the same shapes on the inner axes. So let's see it in action. Let's change the shape of y. So we can change a shape using tf.reshape y, and then we enter the shape that we'd like. In our case, it is currently 3, 2. So maybe we change it to 2, 3. And let's see what happens. Ooh, wonderful. Let's see the original y. Beautiful. So we can see that the 9 has come up to here in this one. And we've now got 10, 11, 12. So this has got 2 rows and 3 columns. Okay. So maybe we go try to multiply x by reshaped y. So x, and we might have to put matrix multiply here so we know what type of multiplication we're doing. X, tf, reshape, y, and then shape 2, 3. Now you see what's happening here? So if we remind ourselves what shape x is shape 3, 2. Let's pay attention only to the shapes. tf.reshape y shape equals 2, 3 dot shape. Paying attention to our rule that the shapes of the inner dimensions, so this tensor multiplied by this tensor, the inner dimensions must match. Does that rule get fulfilled? To me it does, because we've got an inner dimension of 2 here and an inner dimension of 2 here. Let's test it out. Beautiful. It looks like that worked. So we come here, we want to make a new cell. What if we tried to use tf.MatMul on this. So if we go tf.MatMul x tf.reshape, and then we want y shape equals 2, 3. Is this going to work as well? Beautiful. Now we get the same outputs there. Now hold on. Now do you think if we were to reverse this, it would work as well? Now I mean, we reshape x to be a different shape instead of reshaping y. If in doubt, code it out. So x tf reshape x, we're going to change that to be 2, 3 this time. And we're going to not change the shape of y. Let's see what happens. Ah, what happened there? So let's see. We'll just put a little note here. Try change the shape of x instead of y. So you see here how this one has the shape 3, 3, but this one has the shape 2, 2. That's because in this operation, we multiplied two tensors with the shape 3, 2 and 2, 3. So the resulting tensor finishes with the dimensions of the outer dimensions. Whereas in this case, if we go tf.reshape x, shape equals 2, 3, y.shape, we also want the shape here. This is our other rule of matrix multiplication. Because we reshaped x, the resulting matrix here ends up in a shape of 2, 2, because it becomes the outer dimensions. So see here, back to our rule, numbers on the inside must match. New size is the same as outside numbers. Okay, so in both these cases, depending on which tensor we reshaped, the matrix multiplication works, but the resulting output is different. Now, that's a very important point. When you're dealing with matrix multiplication or dot products, it really depends on which tensor you manipulate in terms of what your output would be. So see here how different these two outputs are? Again, we're multiplying the same numbers, but just in different shapes. So that's an important concept to be aware of. And now, we can do the same thing with reshape as with transpose. So let's have a look. This is another important tensor transformation. So can do the same with transpose. However, as you'll see in a second, transpose is slightly different to what reshape is. So transpose, and if we do tf reshape x, shape equals 2, 3. So this is the transpose tensor. They're the same shape as reshaping it. However, you'll notice with the transpose is that, well, let's get x, the first one as well. It starts off as 1, 2, 3, 4, 5, 6. Then the transpose is 1, 3, 5. The odd ones are up the first row, and then 2, 4, 6. And then the reshape is 1, 2, 3, 4, 5, 6. So the difference between transpose and reshape is that transpose flips the axes, whereas reshape just shuffles the tensor around into the shape that you want. So if we go here, TensorFlow transpose, TF transpose, here we go. Transpose A, where A is a tensor. Wow, that's a great description. Permutes the dimensions according to the value of perm. The returns tensor's dimension I will correspond to the input dimension perm I. If perm is not given, it is set to n-1 to 0, where n is the rank of the input tensor. Hence, by default, this operation performs a regular matrix transpose on 2D input tensors. Okay, so we see here 1, 2, 3, 4, 5, 6, transpose. Now the shape is 3, 2. Again, we could try a bunch of different examples, but let's go back and write some different code here. So what we might want to do is, because transpose also changes the shape of our x tensor, let's try matrix multiplication with transpose rather than reshape. So tf MatMul, tf transpose x and y. what might be the output here? Let's find out. 89, 98, 116, 128. Now see how that is different here? Now that is because transpose flips the axes rather than shuffles around the elements of a tensor. This can be quite confusing. However, this kind of data manipulation is a reminder that you're going to spend a lot of your time in machine learning and neural networks reshaping your data in the form of tensors to both prepare it to be used with various operations such as feeding into the model, and once you get it out of the model, to be able to deduce patterns from it and convert it into something human understandable. Now, again, the numbers that we're dealing with are just basically toy numbers. To see an example of how matrix multiplication is actually used, this is a great example. This may seem an odd and complicated way of multiplying, but it is necessary. I'll give you a real-life example to illustrate why we multiply matrices this way. So, example, the local shop sells 3 types of pies, and then we have details here. And if you go through this, this is actually a dot product to work out the value of sales for any given day. Now, this is just a small example here, but in the case of neural networks, they're actually going to go through an absolute multitude of these different numerical transformations to find patterns in our data. The good news is, most of the time, is that once we've set up our neural network code, once we've gotten our tensors into the right shape, a lot of these are done behind the scenes for us. So, with that being said, let's finish this video here. And in the next video, we'll go through a little bit more. We'll really cement down, or we'll get some more practice with transposing and reshaping different matrices and practicing matrix multiplication. So I'll see you there. We've had a little bit of hands-on practice with matrix multiplication and transposing and reshaping different tensors. We're going to do one more video on it to really nail it down. So let's call this one the dot product. And we want to turn that into a markdown cell. Beautiful. So let's go here. Matrix multiplication is also referred to as the dot product. And now you can perform matrix multiplication using, we want tf.MatMul matrix, which is short for matrix multiplication, or we can do it with tf.Tensor. We haven't seen this one yet, but they essentially do the same thing, just with different parameters. So we come here. We've also gotten hands-on with matrix multiplication using matrix multiplication.xyz, and we've seen this colorful example of the dot product. But let's once again get a little bit more hands-on with some code. So let's see how we might use tensor dot. Again, I'm spelling tensor wrong. I'm going to do that throughout this whole course, aren't I? There we go. So perform the dot product on x and y. Now this requires x or y to be transposed. We've also seen how transposing results in different outputs than reshaping. And transposing is flipping the axis, whereas reshaping is just reshuffling. So if we come here and if we reset this, I want you to have a guess at what type of operation this is. Is this a reshape if I go like that and flip it? Or is that a transpose? I'll give you a hint. What did we do? We had to flip the axes to get it up like that. So in that case, it's going to be a transpose. Now, let's use tf.Tensor. And actually, before we do that, let's remind ourselves of what x and y are. X is a tensor of shape 3 and 2, and y is a tensor of shape 3, 2. They have increasing elements from 1 through to 12. Beautiful. Now, if we go tf transpose x and y, oh, I've typed y as a mini case. There we go. Tensor dot. Oh, missing argument axes. So we want to type in on the first axis. Beautiful. 89, 98, 116, 128. Now, if we look up tf tensor dot, what is this going to tell us? Tensor contraction of A and B along specified axes and outer product. Tensor dot, also known as tensor contraction, sums the product of elements from A and B over the indices specified by A axes and B axes. Now, again, you can read through this if you'd really like to, or you can practice coding it. I would suggest doing both. Now, in this case, you might notice that we could use transpose or reshape. However, we get different results. Now, let's try matrix multiplication by transposing Y and reshaping Y. We've done it with X. Let's try it with Y. So perform matrix multiplication. There's going to be a lot of repetition when manipulating tensors because we want to get practice. Y transposed. So tf matmul, let's take X and we'll transpose Y. Transpose, there we go. Now perform matrix multiplication between X and Y reshaped. tf.matmul. You might be wondering why I'm just continually showing you different ways of manipulating matrices. It's because you're going to spend a lot of your time reshaping tensors and matrices into the shape that you want them. So if we can get as much hands-on experience as we can, it might not mean too much to us now because we're just working with toy data. It means later on down the track when we have to reshape and manipulate our tensors and matrices, is that we've got all of this practice under our belt. Wonderful. So we see we get different results from transpose and reshape. Now, to really demonstrate the fact here, or the fact that calling reshape and transpose on Y don't necessarily result in the same values, is that we're going to go through the same steps we did up here before for X. But let's make it a little bit more pretty. So check the values of Y. This is how I really try to understand things. And transposed Y. So if I am writing some code, as I've said before, and I'm wondering why I'm getting different outputs of my tensors and the calculations that I'm making aren't really sort of making sense in my head. By the way, this /n is for new line. As I've said, one of the most common errors you're going to get in writing neural network code is misshaped tensors. And even more like sort of just as common, but deceiving error that is when your tensors line up with shape, but the outputs that you're getting, so you get no error message, it just works. So it's important then to be able to investigate what's going on and figure out, that's called a silent error, is that when your code works, like no error gets outputted from the code itself, but the results just clearly aren't correct. So this is the sort of thing that I will do to investigate those silent errors. TF transpose Y, that's what we want to do. So I'll create some sort of print statement like this, and then I'll use this to really get my head around what's going on. So this is our normal Y, 7, 8, 9, 10, 11, 12, beautiful. Now this is reshaped, again, just reshuffled. We bring the 9 up here, we move the 10 across, the 11 comes up there, the 12 goes on there, so 7, 8, 9, 10, 11, 12, beautiful. Now this is the transposed, so all we've done here is just flip the axes. Let's recreate this one, nice and simple. So 7, 8, 9, 10, 11, 12 over here. We'll just let that run through. This is a great way to just visualize. Let me reset this. 7, 8, 9, 10, 11, 12. Okay, we come back to this tab. You see how we've just got the same tensor here, 7, 8, 9, 10, 11, 12. This is the same over here, beautiful. Now watch, this is a transpose. We're going to bring this up, flip it, boom. That's what has happened here. You see? Except this one is upside down in this case. So it just displays it slightly differently, but the shape and where the values end up, in this case, is what's going to happen if we were to write, say, some code like this. So if we go tf.matmul x tf transpose Y. Beautiful. There we go. So this is a sort of investigative work that we do. We've had a fair bit of practice now transposing and reshaped. If you're still unclear what the difference is between transpose and reshape, or you're wondering Which one should I use? Well, most of the time, these operations will be done behind the scenes for you. So if you write neural network code, it's going to do a lot of matrix multiplication behind the scenes to figure out different patterns in numbers. What sort of patterns are they? Well, remember, here's a simple example of the kind of patterns you can work out with matrix multiplication. But again, it'll be different depending what problem you're working on. But generally, whenever you're performing a matrix multiplication on two different tensors and the shapes of the matrices or tensors don't line up, you will transpose one of the tensors rather than reshaping them. So I'll write that here. Generally, when performing matrix multiplication on two tensors and one of the axes doesn't line up, you will transpose rather than reshape one of the tensors to satisfy the matrix multiplication rules. Alrighty. So again, if there's anything that doesn't quite stick out or make sense, I would definitely encourage you to create a whole bunch of different tensors. Try to use tf MatMul on them. Try to use tensor.Dot if you want, or try to even use the at operator between them. Generally, if we're using TensorFlow, we're going to be using MatMul. But get some errors, fix the shapes with transpose and reshape, and see what kind of different outputs you get. So, we've covered matrix multiplication. Now let's have a look at, if we've got the default data type is often int32. So sometimes, depending on what data we're working with, the data type might not be int32. So what if we had to change the data type of a tensor? That's what we'll look at in the next video. I'll see you there. All right, so as we said in a previous video, the default data type of most tensors will be int32, depending on how they've been created. However, sometimes you'll want to change the data type of your tensor. So let's see how we'll do that. So we can create a new tensor with the default data type, which is float32. Yeah, let's start off with float. Now, I just said that the default is int32, but if we go, the default data type will actually depend on what data is inside your tensor. So if there are floats inside your tensor, we will have b.dtype tf.Float32. Now if we create c equals tf.Constant, now in here we want 710, and this is going to be c dtype. int32. Wonderful. So in the current version of TensorFlow that I'm using, which is TF, I believe it's 2.3 version, 2.3.0, you may have a slightly different version depending on when you're watching this video. At this time, if we create a tensor with floats inside it, they're going to be a float32 type. And if we create a tensor with integers inside it, they're going to be of tf.int32 type. Now, let's say if we wanted to change from float32 to float16. Now, this is called reduced precision. Let's go 32-bit precision. What does this mean? So I'm reading a book about OpenGL ES development. A float in Java has 32 bits of precision, while a byte has 8 bits of precision. This might seem like an obvious point to make, but there are 4 bytes in every float. Okay. So that's in Java. That's not what we want. So 32-bit precision tensor versus 16-bit precision tensor. Mixed precision. Here we go, TensorFlow. Why did we ever doubt the TensorFlow documentation for having something? Mixed precision is the use of both 16 and 32-bit floating point types in a model during training to make it run faster and use less memory. Okay. By keeping certain parts of the model in 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of evaluation metrics such as accuracy. Using this guide, This API can improve performance by more than 3 times on modern GPUs and 60% on TPUs. Today, most models use float32 dtype, which takes 32 bits of memory. There we go. However, there are 2 lower precision dtypes, float16 and bfloat16, each which takes 16 bits of memory instead. Beautiful. Modern accelerators can run operations faster in the 16-bit dtypes. Okay, so the main takeaway from this is that in TensorFlow, the default is 32-bit precision, right? However, we can also do, with modern pieces of hardware, we can also do float16, which takes 16 bits of memory instead. And modern accelerators, which are talking about hardware accelerators, so when we run our code on hardware, can run operations faster in the 16-bit dtypes. That is what's exciting. So, in our case, if we wanted to change our numbers from 32-bit precision, in other words, storing this tensor in 32 bits on memory, we wanted to change it to float16, how might we do that? Well, let's have a look. We can use tf.cast, and then we're going to pass it our original tensor, and then its new dtype is going to be tf.Float16. Oh, and then we want to do b, find out b. Wonderful, dtype equals float16. The original b, what we might do is type out b, and then b.dtype. So we'll reinstantiate b up here. Or maybe it's better just to go d here. Yeah, that's a better idea, Daniel. Wonderful, look at that. We got float32, and now d is the same as b, but it's been stored as float16. So, again, might not matter too much for tensors of only 2 elements, but if we had a tensor of 1,000,000 elements, and we reduced the floating point size from 32 to 16, we've basically halved the amount of space our tensor is taking up on memory, allowing a hardware accelerator to make calculations on it, potentially twice as fast. Now again, that scale may be different because there's a lot of different things that go into computing scale and speeds and whatnot, but that's the concept I want you to imagine, is that although these numbers here take up less space on memory, they may be able to compute faster. And the same thing goes for if we wanted to change from int32 to float32, we can do it in a very similar manner. So let's go change from int32 to float32. So we can go e equals tf.cast. Which one do we make? C dtype equals tf.Float32. Now let's have a look at e. Beautiful. So C was originally, there we go, dtype equals int32 and 710. We just changed it using tf.cast. So E is now, take C and turn it into a float32. Beautiful. And now we can take E float16 equals tf.cast E dtype equals tf float16 E float16. Wonderful. So there are many different data types in TensorFlow. So if you ever come across the need to change your data type of a tensor because some calculations aren't working correctly, tf.cast is going to be your friend. So with that being said, let's have a look in the next video. We're going to go aggregating. We'll see what that means. So have a play around with this one. Create some tensors of float type, of integer type, and then change them from, you can go from float32 to float16, or you could go from int32 to float32. See how many different combinations of data type you can create and change before we see how we can aggregate our tensors. If your data is stored in some sort of tensor format, finding patterns in those tensor formats often involves manipulating tensors. Now, again, when building models in TensorFlow, much of the pattern discovery within tensors is done for you. However, oftentimes that pattern discovery is through the extended use of a few basic operations. So let's start getting into those, otherwise known as tensor operations. We'll start off with basic Operations. Now, do we have a tensor? So you can add values to a tensor using the addition operator. And by the way, when I say basic operations, I'm talking about the default Python operators such as plus, minus, multiplication, and then if we want divide, we can go like that. Right, so we can add values to a tensor using the addition operator. So let's create a tensor equals tf.Constant, and we might make it 10.7, my favorite, and 3.4. And now if we go here, plus 10, what do you think will happen? So this is our tensor here. And if we just use the basic operation of tensor plus 10, wonderful. We get 10 plus 10 is 20, 7 plus 10 is 17, 3 plus 10 is 13, and 4 plus 10 is 14. Wonderful. Now you'll notice that the original tensor is unchanged. This is important because when we're manipulating tensors, we don't necessarily always want to change the underlying tensor. The only way it'll change is if we go tensor equals tensor plus 10. We'll reset it. Now this is going to be plus 20, isn't it? There we go. We'll come back here. And there we go, tensor. But if we got rid of this, tensor, we rerun this cell. Oh, invalid syntax. And then we rerun this one. We still get the same values as what our original tensor was. And we might just press enter there so it's more succinct with how it comes out. Beautiful. So, of course, other operations also work. So multiplication also works. So if we wanted to go tensor times 10, same thing. We get 100 because 10 times 10, 100, 70, 30, 40, etc. And then subtraction if you want. So tensor minus 10 can go into the negatives. That's no problem. Tensors can store a whole range of different values. In addition to the operators, like the Python operators, we can also use an equivalent TensorFlow function. Now, what this means is that if we do use the TensorFlow function, so that means we're accessing the TensorFlow library. Let me just show you, because it's easier to talk about something if we can see it. We can use the TensorFlow built-in function too. So tf.multiply, and we want, see here, we get the doc string here. We get tf.mat.multiply, so we'll have a look at that in a moment, but I just want to demonstrate it to you. Tensor 10. We get the same output here. So if we go here, let's look up tf.math.multiply. So for a lot of these tf.math functions, so tf.math, we can do the alias of just tf multiply. So if we go tf multiply, it's just going to lead us to the same thing. Wonderful. Now, does it say here what the benefits are? It doesn't quite. But what I'm going to get you to do is just trust me here when I say that if you have to do some sort of tensor operation like this, and again, usually a lot of these will be done behind the scenes for you. But if you want your code to be sped up on a GPU, typically it gets sped up when you use the TensorFlow version of some sort of operator. So if we wanted to do addition, I mean, this is going to be very fast because it's only a small tensor. And we could do tensor plus 10. But if you want to have the advantages of TensorFlow built into your basic operations, use the tf math something tensor to manipulate your tensors. But here, again, even though we've used the TensorFlow function here, the original tensor is still unchanged. So these are the basic operators. Create some tensors, have some practice at running the addition, minus, multiplication, and division on them, and also do the equivalence of tf.multiply or tf.addition or something like that. Is it tf.addition? tf math addition? Or is it just add? Yeah, add. Okay. That's your little homework for this brief video here. But in the next one, we're going to have a look at a very important concept in neural networks, and that is matrix multiplication. We'll see how to do that with tensors. So we left off in the last video figuring out how we can manipulate our tensors with the basic operations. And so hopefully you've tried out a few of these for yourself. But now we're going to go on to matrix multiplication. So in machine learning, matrix multiplication is one of the most common tensor operations. So the ones we've been through already, these basic operations, are often referred to as element-wise operations. So that means that if we go here, for the addition, for example, we've got our tensor here, which is 10, 7, 3, 4. Now, element-wise means go through one element at a time and just add 10. So this element, add 10. This element, add 10. This element, add 10. This element, add 10. But there's a few different types. So matrix multiplication and the dot product are not necessarily element-wise. So if we go here, what is matrix multiplication? How to multiply matrices. Math is fun. I really like this domain name, actually. Let's have a look here. A matrix is an array of numbers. To multiply a matrix by a single number is easy. So 2 times 4 equals 8. Yes. That's what we've done, right? So that's element-wise. So 2 times 0 equals 0, 2 times 1 equals 2, 2 times -9 equals -18. Beautiful. However, what if we wanted to multiply a matrix by another matrix? And remember, because we're using TensorFlow, even though this is a matrix, we're referring to them as tensors as well. So I want you to read this as matrix and tensor interchangeable. But to multiply a matrix by another matrix, we need to do the dot product of rows and columns. What does that mean? Let's see an example. So the dot product is the first row and the first column. Okay, so we've got a row here times this column equals 58. Okay. The dot product is where we multiply matching members, then sum them up. So 1, 2, 3 times 7, 9, 11. Okay, 1, 2, 3 times 7, 9, 11, yes. Equals 1 times 7. Okay, yep. 2 times 9. Yeah, 2 times 9. 3 times 11. Okay, I've got that. That equals 58. Then we do it again for the second column, and that's 64. And then again, again, again. A great website I like to visualize this is, I believe, matrix multiplication.xyz. We'll go to that. So here, beautiful. We can even customize these. So we'll go here, 1, 2, 7, my favorite number, 7, 2, 1, just to be fancy. And then maybe 3, 3, 3, because I like 3 as well. And then this can just stay the same. So might zoom in here. So let's go multiply. What happens? Whoa, we get some. So that tensor just came up there and jumped on top of that. And then if we go through, we go 1 times 2, 2 times 6, 7 times 1. Okay, so that's 2 plus 12 plus 7. How did this get to 21? 2 plus 12 plus 7. We might try a different set of numbers. How did that work? 5. Maybe our matrix multiplication demo is busted. Multiply. Let's try. 1 times 3 plus 12 plus 5. Does that make sense? So 3, 12 plus 5. Yeah, that makes sense. 15. So this is 3 plus 12 is 15 plus 5 is 20. There we go. And if we step through there, step through, step through, wow, we get the output there. Before we even start to write code, go to this website, start practicing around, see what happens. And after you've done that for about a minute or so, or maybe 3 minutes, give yourself a few different goes. Let's go back to the notebook and see how we can do this exact operation in TensorFlow code. So I'll give yourself a second there, but I'm going to start coding so you can pause the video now if you want, try out that website and come back. So let's see matrix multiplication in TensorFlow. What if we just Google that? Matrix multiplication in TensorFlow. MatMul. There we go. tf.linalg, which is short for linear algebra, .matmul. Multiplies matrix A by matrix B, producing A times B. A, B. And we get a whole bunch of documentation, which is beautiful. We could read through that, or we could write the code ourselves. So, what do we have? Do we have a tensor? Print our tensor. We can print it if we want. Print. Yes, we do. Now, tf matmul. Now, for a lot of these operations, you can usually drop the intermediary here. So, linalg. This is a little trick of TensorFlow. You can just do tf.matmul, which is what I'm about to do here. tf matmul, tensor, tensor. Can we matrix multiply those? Oh, yes, we can. Wonderful. We get 121, 98, 42, 37. Beautiful. Now, if you wanted to do the matrix multiplication, Python has an operator, A. Now, you see how the outputs here actually are different to if we just did, what if we did tensor times tensor? We get different outputs here. Okay. Because if we have a look at our tensor again, this is element-wise. So it's just gone 10. Maybe we'll print it out twice. 10 times 10 is 100. 7 times 7 is 49. 3 times 3 is 9. 4 times 4 is 16. Whereas with matmul, we've gone in this fancy little way here. So maybe, I've got an idea. We recreate this tensor. That could be a little exercise for you as well, is to recreate this tensor in TensorFlow and recreate this tensor in TensorFlow. So the same elements in the same shape. This would be a what? 1, 2, 3, a 3 by 3 tensor. And this would be a 1, 2, 3 by 2 tensor, so 3 by 2. And then run tf.matmul on left tensor, right tensor. See if you get the same outputs as here. But we come back here. If you wanted to do matrix multiplication with a Python operator, we can do tensor at tensor. So the at symbol in Python actually is for matrix multiplication. Now, both of these examples work because our tensor variable, this is an important fact. This is where we come in and we check the shapes attribute. Because our tensor.shape attribute is 2 and 2. So both of them have the same shape of 2 and 2. But what if we wanted to do matrix multiplication on tensors which had differing shapes? Now, rather than just think about it, let's try. So create a tensor of maybe 3, 2. Similar to this one here. So this is 3, 2. Remember, rows come first. 1, 2, 3. Columns, 1, 2. Let's create a similar one. Create a 3, 2 tensor equals tf.constant. And we want 1, 2. We'll keep this one nice and simple. 3, 4, 5, 6. Beautiful. And then we want create another 3, 2 tensor. And in this case, it can be y, tf, constant, and we'll just increase this one. So that can go from 7, 8, 9, 10, 11, 12. Wonderful. Let's have a look at both of those. X, Y. Okay, so we've got two tensors here, both of the same shape, 3 by 2, and they got slightly differing elements. Now, what if we tried to matrix multiply them? So let's try to matrix multiply tensors of same shape. We could do it like that. See what happens? Oh, matrix size incompatible. In 3, 2, in 3, 2. What if we try the tf matmul? What happens here? X, Y. Invalid. Matrix size incompatible. Same thing. 3, 2, in 0. So this is our first element here, our 0th element. And this is our other element here. our first element, which is also 3, 2. This is where we have two rules for matrix multiplication. Do these websites tell us? Why do we do it this way? Actually, this is a great example. I'm going to put this as an external resource if we come back. If you ever see this emoji in the course, this is a resource. So resource, info, and example of matrix multiplication. So check that out. If you ever see that little book emoji, that's an external resource that I definitely recommend. Now, let's go back to here. Why doesn't this work? I don't think this web page explicitly states it, but I'm going to tell you anyway. You can look this up. You'll find this wherever you find matrix multiplication, is that there is a couple of rules that our tensors or matrices need to fulfill. So come up here. Let's put in here. There are two rules our tensors or matrices need to fulfill if we're going to matrix multiply them. Now, rule 1, the inner dimensions must match. And rule 2, the resulting matrix has the shape of the inner dimensions. So knowing these two rules, I'm going to set you a challenge. Is before the next video, we're going to go through these two rules and see how we can fix our problem here. But considering these two tensors, so we've got, if I say rule 1 is that the inner dimensions must match, what are the inner dimensions here? Maybe 2 and 3, they don't really match. So how would we get this, the inner dimensions of these two matrices to match? That's your challenge. If you're not sure, that's completely fine, but that's your challenge before the next video. If you can get it done, amazing work. If not, we're going to go through that in the next video. So I'll see you there. In the last video, we kind of left off on an error. And we said in this video that we're going to fix it. So let's do that. Now we tried to matrix multiply two tensors of the same shape, specifically x and y. They're both of the shape 3, 2. And we've got this little error here saying n0 is 3, 2 and n1 is 3, 2. So matrix size incompatible. So if we come up here, back to the rules we set ourselves, the inner dimensions must match. And the resulting matrix has the same shape of the inner dimensions. Now, if you had a go at fixing this and you got through it, excellent work. You may want to skip over this lecture. However, if you didn't make it, that's completely fine. Matrix multiplication takes a little while to get your head around. If we come over here, I've got a slide. Matrix multiplication is also known as the dot product. So when we call the code tf.MatMul, and we have a matrix of some size here and a matrix of some size here, remember, a lot of the operations that we do can be on matrices or tensors of an arbitrary size, but just for illustration purposes, I've done this size here. So here's our first rule. So numbers on the inside must match. And there's our second rule. New size is the same as outside numbers. Okay. So if we come back, does that line up with what we've said here? The inner dimensions must match. The resulting matrix has the same shape of the inner dimensions. Oh no. Of the outer dimensions. There we go. Getting our own rules incorrect. So we come back. Let's have a look at what's going on here. We've got tf.MatMul. We've got one matrix or tensor here, A, B, C, D, E, F, G, H, I, which is the shape of 3 by 3. Wonderful. And this will run because the numbers on the inside match. See these two 3s here with the red background? And this is of shape 3, 2. So 1, 2, 3, and 2 columns. Okay, so that matches. And then we're going to result in here. If we did the dot product, which is the same as matrix multiply in TensorFlow, we have A times J plus B times L plus C times N. And then we follow through with that rule for every single cell in these two, or every single element in these two tensors. And now the new size is 3 by 2. 1 row, 2 row, 3 row, 2 columns, which is the blue numbers here. Okay, wonderful. And then if we swap these elements from letters to actual numbers, so the same shapes here, we take 5 times 4. Okay, this is the same as A times J. Yes. 0 times 6. Okay, 0 times 6. Yes, which is the same as B times L. Wonderful. And then we have 3 times 8. Which is the same as C times N. All right. Now, again, looking at these diagrams, they're quite, for the first, I would say, 20, 30, 50 times you look at dot products and matrix multiplications, it takes a lot of repetition to get used to. But then if we have 5 times 4 equals 20, plus 0 times 6 equals 0, plus 3 times 8 equals 24, so we add these three up, we get 44 in the top left. Repeat the same for each element, and we get this resulting matrix here. Now, the live demo we've already had a look at. Matrix multiplication.xyz. This is what's happening here. If we reset and multiply, we take that, we flip it on the top, then we go here, we get 20, and we get the next two elements, and the next two, and the next one. So this is a moving diagram of what's going on here. So let's go back to our code. Let's fix it up. Let's make it work. So knowing our two rules, number one, that the inner dimensions must match, and that the resulting matrix is the same shape as the outer dimensions, how might we get this to work? Well, we're either going to have to change the shape of this matrix or change the shape of this matrix. Again, I'm using the term matrix and tensor interchangeably here. Or we're going to just have to create an entirely new tensor with the same shapes on the inner axes. So let's see it in action. Let's change the shape of y. So we can change a shape using tf.reshape y, and then we enter the shape that we'd like. In our case, it is currently 3, 2. So maybe we change it to 2, 3. And let's see what happens. Ooh, wonderful. Let's see the original y. Beautiful. So we can see that the 9 has come up to here in this one. And we've now got 10, 11, 12. So this has got 2 rows and 3 columns. Okay. So maybe we go try to multiply x by reshaped y. So x, and we might have to put matrix multiply here so we know what type of multiplication we're doing. X, tf, reshape, y, and then shape 2, 3. Now you see what's happening here? So if we remind ourselves what shape x is shape 3, 2. Let's pay attention only to the shapes. tf.reshape y shape equals 2, 3 dot shape. Paying attention to our rule that the shapes of the inner dimensions, so this tensor multiplied by this tensor, the inner dimensions must match. Does that rule get fulfilled? To me it does, because we've got an inner dimension of 2 here and an inner dimension of 2 here. Let's test it out. Beautiful. It looks like that worked. So we come here, we want to make a new cell. What if we tried to use tf.MatMul on this? So if we go tf, MatMul, x, tf.reshape, and then we want y shape equals 2, 3. Is this going to work as well? Beautiful. Now we get the same outputs there. Now hold on. Now do you think if we were to reverse this, it would work as well? Now I mean, we reshape x to be a different shape instead of reshaping y. If in doubt, code it out. So x, tf, reshape x, we're going to change that to be 2, 3 this time. And we're going to not change the shape of y. Let's see what happens. Ah, what happened there? So let's see. We'll just put a little note here. Try change the shape of x instead of y. So you see here how this one has the shape 3, 3, but this one has the shape 2, 2. That's because in this operation, we multiply two tensors with the shape 3, 2 and 2, 3. So the resulting tensor finishes with the dimensions of the outer dimensions. Whereas in this case, if we go tf.reshape x, shape equals 2, 3, y dot shape, we also want the shape here. This is our other rule of matrix multiplication. Because we reshaped x, the resulting matrix here ends up in a shape of 2, 2, because it becomes the outer dimensions. So see here, back to our rule, numbers on the inside must match. New size is the same as outside numbers. Okay, so in both these cases, depending on which tensor we reshaped, the matrix multiplication works, but the resulting output is different. Now, that's a very important point. When you're dealing with matrix multiplication or dot products, it really depends on which tensor you manipulate in terms of what your output would be. So see here how different these two outputs are. Again, we're multiplying the same numbers, but just in different shapes. So that's an important concept to be aware of. And now we can do the same thing with reshape as with transpose. So let's have a look. This is another important tensor transformation. So we can do the same with transpose. However, as you'll see in a second, transpose is slightly different to what reshape is. So transpose, and if we do tf reshape x, shape equals 2, 3. So this is the transpose tensor. They're the same shape as reshaping it. However, you'll notice with the transpose is that, well, let's get x, the first one as well. It starts off as 1, 2, 3, 4, 5, 6. Then the transpose is 1, 3, 5. The odd ones are up the first row, and then 2, 4, 6. And then the reshape is 1, 2, 3, 4, 5, 6. So the difference between transpose and reshape is that transpose flips the axes, whereas reshape just shuffles the tensor around into the shape that you want. So if we go here, TensorFlow transpose, TF transpose, here we go. Transpose A, where A is a tensor. Wow, that's a great description. Permutes the dimensions according to the value of perm. The returned tensor's dimension I will correspond to the input dimension perm I. If perm is not given, it is set to n-1 to 0, where n is the rank of the input tensor. Hence, by default, this operation performs a regular matrix transpose on 2D input tensors. Okay, so we see here 1, 2, 3, 4, 5, 6, transpose. Now the shape is 3, 2. Again, we could try a bunch of different examples, but let's go back and write some different code here. So what we might want to do is, because transpose also changes the shape of our x tensor, let's try matrix multiplication with transpose rather than reshape. So tf MatMul, tf transpose x and y. What might be the output here? Let's find out. 89, 98, 116, 128. Now see how that is different here? Now that is because transpose flips the axes rather than shuffles around the elements of a tensor. This can be quite confusing. However, this kind of data manipulation is a reminder that you're going to spend a lot of your time in machine learning and neural networks reshaping your data in the form of tensors to both prepare it to be used with various operations such as feeding into the model, and once you get it out of the model, to be able to deduce patterns from it and convert it into something human understandable. Now, again, the numbers that we're dealing with are just basically toy numbers. To see an example of how matrix multiplication is actually used, this is a great example. This may seem an odd and complicated way of multiplying, but it is necessary. I'll give you a real-life example to illustrate why we multiply matrices this way. So, example, the local shop sells 3 types of pies. and then we have details here. And if you go through this, this is actually a dot product to work out the value of sales for any given day. Now, this is just a small example here, but in the case of neural networks, they're actually going to go through an absolute multitude of these different numerical transformations to find patterns in our data. The good news is, most of the time, is that once we've set up our neural network code, once we've gotten our tensors into the right shape, a lot of these are done behind the scenes for us. So, with that being said, let's finish this video here. And in the next video, we'll go through a little bit more. We'll really cement down, or we'll get some more practice with transposing and reshaping different matrices and practicing matrix multiplication. So I'll see you there. We've had a little bit of hands-on practice with matrix multiplication and transposing and reshaping different tensors. We're going to do one more video on it to really nail it down. So let's call this one the dot product. And we want to turn that into a markdown cell. Beautiful. So let's go here. Matrix multiplication is also referred to as the dot product. And now you can perform matrix multiplication using, we want tf.MatMul matrix, which is short for matrix multiplication, or we can do it with tf.Tensor. We haven't seen this one yet, but they essentially do the same thing, just with different parameters. So we come here. We've also gotten hands-on with matrix multiplication using matrix multiplication.xyz, and we've seen this colorful example of the dot product. But let's once again get a little bit more hands-on with some code. So let's see how we might use tensor dot. Again, I'm spelling tensor wrong. I'm going to do that throughout this whole course, aren't I? There we go. So perform the dot product on x and y. Now this requires x or y to be transposed. We've also seen how transposing results in different outputs than reshaping. And transposing is flipping the axis, whereas reshaping is just reshuffling. So if we come here and if we reset this, I want you to have a guess at what type of operation this is. Is this a reshape if I go like that and flip it? Or is that a transpose? I'll give you a hint. What did we do? We had to flip the axes to get it up like that. So in that case, it's going to be a transpose. Now, let's use tf.Tensor. And actually, before we do that, let's remind ourselves of what x and y are. X is a tensor of shape 3 and 2, and y is a tensor of shape 3, 2. They have increasing elements from 1 through to 12. Beautiful. Now, if we go tf transpose x and y, oh, I've typed y as a mini case. There we go. Tensor dot. Oh, missing argument axes. So we want to type in on the first axes. Beautiful. 89, 98, 116, 128. Now, if we look up tf tensor dot, what is this going to tell us? Tensor contraction of A and B along specified axes and outer product. Tensor dot, also known as tensor contraction, sums the product of elements from A and B over the indices specified by A axes and B axes. Now, again, you can read through this if you'd really like to, or you can practice coding it. I would suggest doing both. Now, in this case, you might notice that we could use transpose or reshape. However, we get different results. Now, let's try matrix multiplication by transposing y and reshaping y. We've done it with x. Let's try it with y. So, perform matrix multiplication. There's going to be a lot of repetition when manipulating tensors because we want to get practice. Y transposed. So tf.MatMul, let's take x and we'll transpose y. Transpose, there we go. Now perform matrix multiplication between x and y reshaped. tf.MatMul. You might be wondering why I'm just continually showing you different ways of manipulating matrices. It's because you're going to spend a lot of your time reshaping tensors and matrices into the shape that you want them. So if we can get as much hands-on experience as we can, it might not mean too much to us now because we're just working with toy data. It means later on down the track when we have to reshape and manipulate our tensors and matrices, is that we've got all of this practice under our belt. Wonderful. So we see we get different results from transpose and reshape. Now, to really demonstrate the fact here, or the fact that calling reshape and transpose on y don't necessarily result in the same values, is that we're going to go through the same steps we did up here before for x. But let's make it a little bit more pretty. So check the values of y. This is how I really try to understand things. And transposed y. So if I am writing some code, as I've said before, and I'm wondering why I'm getting different outputs of my tensors and the calculations that I'm making aren't really sort of making sense in my head. By the way, this /n is for new line. As I've said, one of the most common errors you're going to get in writing neural network code is misshaped tensors. And even more like sort of just as common, but deceiving error that is when your tensors line up with shape, but the outputs that you're getting, so you get no error message, it just works. So it's important then to be able to investigate what's going on and figure out, that's called a silent error, is that when your code works, like no error gets outputted from the code itself, but the results just clearly aren't correct. So this is the sort of thing that I will do to investigate those silent errors. TF transpose y, that's what we want to do. So I'll create some sort of print statement like this, and then I'll use this to really get my head around what's going on. So this is our normal y, 7, 8, 9, 10, 11, 12, beautiful. Now this is reshaped, again just reshuffled. We bring the 9 up here, we move the 10 across, the 11 comes up there, the 12 goes on there, so 7, 8, 9, 10, 11, 12, beautiful. Now this is the transposed, so all we've done here is just flip the axes. Let's recreate this one, nice and simple. So 7, 8, 9, 10, 11, 12 over here. We'll just let that run through. This is a great way to just visualize. Let me reset this. 7, 8, 9, 10, 11, 12. Okay, we come back to this tab. You see how we've just got the same tensor here, 7, 8, 9, 10, 11, 12. This is the same over here, beautiful. Now watch, this is a transpose. We're going to bring this up, flip it, boom. That's what has happened here. You see? Except this one is upside down in this case. So it just displays it slightly differently, but the shape and where the values end up, in this case, is what's going to happen if we were to write, say, some code like this. So if we go tf.MatMul x tf transpose y. Beautiful. There we go. So this is a sort of investigative work that we do. We've had a fair bit of practice now transposing and reshaped. If you're still unclear what the difference is between transpose and reshape, or you're wondering, which one should I use? Well, most of the time, these operations will be done behind the scenes for you. So if you write neural network code, it's going to do a lot of matrix multiplication behind the scenes to figure out different patterns in numbers. What sort of patterns are they? Well, remember, here's a simple example of the kind of patterns you can work out with matrix multiplication. But again, it'll be different depending what problem you're working on. But generally, whenever you're performing a matrix multiplication on two different tensors and the shapes of the matrices or tensors don't line up, you will transpose one of the tensors rather than reshaping them. So I'll write that here. Generally, when performing matrix multiplication on two tensors and one of the axes doesn't line up, you will transpose rather than reshape one of the tensors to satisfy the matrix multiplication rules. Alrighty. So again, if there's anything that doesn't quite stick out or make sense, I would definitely encourage you to create a whole bunch of different tensors. Try to use tf MatMul on them. Try to use tensor.dot if you want, or try to even use the at operator between them. Generally, if we're using TensorFlow, we're going to be using MatMul. But get some errors, fix the shapes with transpose and reshape, and see what kind of different outputs you get. So, we've covered matrix multiplication. Now let's have a look at, if we've got the default data type is often int32. So sometimes, depending on what data we're working with, the data type might not be int32. So what if we had to change the data type of a tensor? That's what we'll look at in the next video. I'll see you there. All right, so as we said in a previous video, the default data type of most tensors will be int32, depending on how they've been created. However, sometimes you'll want to change the data type of your tensor. So let's see how we'll do that. So we can create a new tensor with the default data type, which is float32. Yeah, let's start off with float. Now, I just said that the default is int32, but if we go, the default data type will actually depend on what data is inside your tensor. So if there are floats inside your tensor, we will have b.dtype tf.Float32. Now if we create c equals tf.Constant, now in here we want 710, and this is going to be c dtype. int32, wonderful. So in the current version of TensorFlow that I'm using, which is tf, I believe it's 2.3 version, 2.3.0, you may have a slightly different version depending on when you're watching this video. At this time, if we create a tensor with floats inside it, they're going to be a float32 type. And if we create a tensor with integers inside it, they're going to be of tf.int32 type. Now, let's say if we wanted to change from float32 to float16. Now, this is called reduced precision. Let's go 32-bit precision. What does this mean? So I'm reading a book about OpenGL ES development. A float in Java has 32 bits of precision, while a byte has 8 bits of precision. This might seem like an obvious point to make, but there are 4 bytes in every float. Okay. So that's in Java. That's not what we want. So 32-bit precision tensor versus 16-bit precision tensor. Mixed precision. Here we go, TensorFlow. Why did we ever doubt the TensorFlow documentation for having something? Mixed precision is the use of both 16 and 32-bit floating point types in a model during training to make it run faster and use less memory. Okay. By keeping certain parts of the model in 32-bit types for numeric stability, the model will have a lower step time and train equally as well in terms of evaluation metrics such as accuracy. Using this guide, this API can improve performance by more than 3 times on modern GPUs and 60% on TPUs. Today, most models use float32 dtype, which takes 32 bits of memory. There we go. However, there are 2 lower precision dtypes, float16 and bfloat16, each which takes 16 bits of memory instead. Beautiful. Modern accelerators can run operations faster in the 16-bit dtypes. Okay, so the main takeaway from this is that in TensorFlow, the default is 32-bit precision, right? However, we can also do, with modern pieces of hardware, we can also do float16, which takes 16 bits of memory instead. And modern accelerators, which are talking about hardware accelerators, so when we run our code on hardware, can run operations faster in the 16-bit dtypes. That is what's exciting. So, in our case, if we wanted to change our numbers from 32-bit precision, in other words, storing this tensor in 32 bits on memory, we wanted to change it to float16, how might we do that? Well, let's have a look. We can use tf.cast, and then we're going to pass it our original tensor, and then its new dtype is going to be tf.Float 16. Oh, and then we want to do b, find out b. Wonderful, dtype equals float 16. The original b, what we might do is type out b, and then b.dtype. So we'll reinstantiate b up here. Or maybe it's better just to go d here. Yeah, that's a better idea, Daniel. Wonderful, look at that. We got float 32, and now d is the same as b, but it's been stored as float 16. So, again, might not matter too much for tensors of only 2 elements, but if we had a tensor of 1,000,000 elements, and we reduced the floating point size from 32 to 16, we've basically halved the amount of space our tensor is taking up on memory, allowing a hardware accelerator to make calculations on it, potentially twice as fast. Now again, that scale may be different because there's a lot of different things that go into computing scale and speeds and whatnot, but that's the concept I want you to imagine, is that although these numbers here take up less space on memory, they may be able to compute faster. And the same thing goes for if we wanted to change from int32 to float32, we can do it in a very similar manner. So let's go change from int32 to float32. So we can go e equals tf.cast. Which one do we make? C dtype equals tf.Float32. Now let's have a look at e. Beautiful. So C was originally, there we go, dtype equals int32 and 710. We just changed it using tf.cast. So E is now, take C and turn it into a float 32. Beautiful. And now we can take E float 16 equals tf.cast E dtype equals tf float 16 E float 16. Wonderful. So there are many different data types in TensorFlow. So if you ever come across the need to change your data type of a tensor because some calculations aren't working correctly, tf.cast is going to be your friend. So with that being said, let's have a look in the next video. We're going to go aggregating. We'll see what that means. So have a play around with this one. Create some tensors of float type, of integer type, and then change them from, you can go from float 32 to float 16, or you could go from int 32 to float 32. See how many different combinations of data type you can create and change before we see how we can aggregate our tensors. Welcome back. Now, after the last video, I took another little break. And so what you see here is when the cell numbers are empty. I just want to show you this. This is, rather than going straight onto the next video in practice, I just want to show you how I actually work with Google Colab notebooks every day, is that when you leave it for a while, all your information in Colab is going to shut down so that Google's compute resources can be allocated to other people who want to use Colab. So you see here, I haven't got a connection. But if I decide to run a single cell, Shift and Enter, it's going to allocate some memory to me, basically a computer in Google's warehouse full of computers somewhere around the world. And once it's ready to go, boom, we're connected. However, if I try to run this cell above here, TF is not defined, so I haven't imported TensorFlow. So what I often do is, we saw this in a previous video, but it'll work better now because see here, we've got 0, 1. These are the first cells I've tried to run in this notebook since taking a break. Let me do, if I wanted to run, I could do restart and run all. So that would run all the cells in this notebook. Or I could just do run before, which is what I usually do. It's going to try and run all of the cells before whichever current cell that you're on. But boom, we get our type error right back up the top here where we created our changeable tensor with tf.Variable. And we deliberately caused an error. So if that happens, your errors are not going to fix themselves, but then we can just go back to here and then we should be able to run all of our cells. I'm just continually pressing Shift and Enter. Should be pretty quick because we're not processing much data here. But we'll go right down to where we were. Aggregating tensors. Oh, we got another error. That's all right. We'll keep going. Oh, we've covered a fair bit of ground here. Are we at? Yes, here we are. So we're back to where we were. So aggregating tensors. Now, let's have a look. What does aggregation mean? Define aggregation. A group, body, or mass composed of many distinct parts or individual. A galaxy is an aggregation of stars and gas. The collecting of units or parts into a mass or whole. The condition of being so collected. Well, that doesn't really help us with understanding tensors, but we're going to see hands-on what aggregation means in the concept of, or in the topic of tensors. So, to me, aggregating tensors equals condensing them from multiple values down to a smaller amount of values. That's how I conceptually understand aggregation. You can create your own definition, and in fact, I actually want you to start doing that more and more with, as you get more familiar with the world of deep learning, is to, of course, there's going to be agreed upon definitions in the field, but I also want you to start conceptualizing your own definitions in a way that you best understand things. But let's see how we might start aggregating our tensors. The first way we're going to do is by getting the absolute values. So this is actually probably not the best form of aggregation to start with, but we're going to include it here anyway, just for completeness. So we create a tensor. What were we up to? E. We might recreate D here, tf.Constant, just because Daniel begins with D, and it's, aside from the number 7, D is probably my favorite. Sorry, number 7 is probably my favorite number, and D is probably my favorite letter. So fun fact about me. There we go, get the absolute values. Beautiful. So, we just created a new tensor, and if we wanted to get the absolute values, we can go tf.abs d. And we'll see what this does. Beautiful. So the absolute values are basically just take all the negative numbers in one tensor and turn them into positive numbers. So if we see here, let's check out the docstring. I'm pressing Shift Command Space to get this docstring. Computes the absolute value of a tensor. Given a tensor of integer or floating point values, this operation returns a tensor of the same type where each element returns the absolute value of the corresponding element in the input. Beautiful, so that's your formal definition. And then we've got some example use cases. So let's actually start to see a few more versions of aggregation. Let's go through the following forms of aggregation. We'll turn that into a markdown cell, and we'll come down here. The first one I want to go through is get the minimum, and then we might want to get the maximum of a certain tensor. We also might want to get the mean of a tensor, and we also might want to get the sum of a tensor. Now, I've shown you a few different ways of how you can explore different methods in TensorFlow. So if you wanted to start with a tensor and find the minimum, the maximum, the mean, or the sum, how might you research? So if we go here, find the mean of a tensor in TensorFlow. Here's a little hint. If you were to search that, you can pause the video now, skip and go ahead and try to create your own tensor, do these 4 things, and then come back and we'll compare notes, all right? But otherwise, if you're going to watch on, let's start by creating a random tensor so that we can practice each of these 4 things here. Create a random tensor. We might create a larger tensor. Yeah, how about we do that? With values between 0 and 100 of, how long should we do it? Of size 50. Let's do that. So E equals tf.Constant. We'll do it using a NumPy random array. So again, this is going to just be return random integers from low inclusive value to high exclusive value. So we can just go 0 to 100, size equals 50. Now this should give us a tensor. Beautiful. 50 values between 0 and 100. And we might go, how do we check the size of our tensor? Let's practice. And then how do we check the shape of our tensors? And then how do we check how many number of dimensions our tensor has? Beautiful. So we get size is 50, beautiful. The shape is also 50, and the number of dimensions is 1. All right. Now, how about we start with finding the minimum? So we're going to go find the minimum. To find the minimum of a tensor, you can do reduce min, pass it a tensor. Put the output there. Now, this is going to be a little bit of a trend with TensorFlow aggregation, is that the reduce underscore, in some, like NumPy, if we did MP min, I believe, we can just go 0. But TensorFlow tends to put reduce underscore min in front of its aggregation methods here. So we'll get rid of that one. So knowing that this is the way to find the minimum, how do you think we might find the maximum? Let's find it anyway. Find the maximum. TF reduce max. Wonderful. So there's 97. So that makes sense because we have values between 0 and 100. So our lowest value so far is 0, and the highest value is 97. And find the mean. Let's go TF reduce mean of E. And wonderful. So 48 is about the average. So get the sum of a tensor. Let's have a guess. Find the sum. TF reduce underscore sum of E. And there is the sum of our tensor. Beautiful. Now, there's a few other things that we can do, such as I'm going to put a little challenge here. I want you, of our E tensor, before the next video, I'm going to put a little emoji here. Exercise is to, with what we've just learned, find the variance and standard deviation of our E tensor using TensorFlow methods. So, if you're not sure what variance and standard deviation are, this challenge has two sides to it. First, you have to find the code to find the variance of our E tensor, and then you have to look up what variance and standard deviation are. So, go and give that a try, and I'll see you in the next video. We finished up the last video with a little challenge. So, did you figure it out? Did you find the variance and standard deviation of our E tensor using TensorFlow methods? I hope you gave it a try, but if not, we're going to check it out here. So find the variance of our tensor. Now, as you might have guessed, we can do TF reduce var E. Oh, has no method reduce var. Is it variance? Has no method reduce variance. Oh, TensorFlow variance. I typed TensorFlow wrong. Ah. Okay, we can do the reduce standard deviation. Have I led you on a wild goose chase? Yes, I totally meant for all this to happen. TFP. So what we might need to do is, what's TFP? This is what I like to do, is just figure out, go down the rabbit hole. TFP, TensorFlow probability. Okay. How do we import it? Can we do import TensorFlow probability as TFP? There we go. And then we might do tfp.stats.reduce variance of E. What was that method again? We come back here. This is the type of research I want you to start practicing. Okay, tf.stats.variance. There we go. Wonderful. Okay, so there's a variance there. I'm going to put here, won't work. And then if we wanted to find the standard deviation, so let's put a little note here actually. To find the variance of our tensor, we need access to TensorFlow probability. And then we go here, find the standard deviation. See, I thought that you would be able to just do reduce variance. So I've learned something there too. Apparently, we need TensorFlow probability to find the variance. Now, I believe we can find the standard deviation here. Reduce STD. Ah, what's happened here? TF math reduced STD. Does it not have an alias? What if we do tf.math.reduce STD? Must be either real or complex. So if we come here, input tensor. What's wrong with our tensor? Reduces input tensor along the given axis. Unless keep dims is true, the rank of the tensor is reduced by 1. Input tensor, the tensor to reduce, should have real or complex type. Does it have to be a float? This is a good little challenge. I'm glad I issued this exercise. We can work this out together. So where's our, here, dtype int 64. You know what I think this method might need? Is if we cast our E tensor as dtype tf int 32, this might work. Int 32. Input must be real or complex. Maybe float 32. There we go. Okay. So this is what I mean. Things may not be as they appear when you go through the TensorFlow library. So up here, we've got a few relatively easy methods compared to what we had to do here. But this has been a great practice as to how you might go about researching and trying things out to make something work. So if you ever get that error that we got just before, let's write this again. So tf math.reduce std e for our tensor. So type error. If you ever get the type error message, come to the documentation, which is what we did here. All right, so there's tf math reduce std. And check out the types that they're using in the example workflows. So see here, the reason why I picked up that we might need to change our tensor to data type float 32 is because they're using floats in their input sample here. So there we go. Returns the reduced tensor of the same dtype as input tensor. Note for complex or complex 128 input, the return tensor will be of type float 32 or float 64 respectively. So usually, a lot of the time when you're working with TensorFlow, float 32 is generally sort of the standard type throughout the entire library. So if you need to change the type of your tensors, chances are it might have to be in float 32. But that was a good practice in exploration. Now in the next video, let's see how we're going to find the positional maximum and minimum. You might want to try this out now that you've had your expert problem-solving skills upgraded in this video. See how you might find the positional maximum and minimum of a tensor. I'll see you in the next video. So I was all ready for this video to jump straight into finding the positional maximum and minimum. However, after a little bit more exploration of the TensorFlow documentation, which can be a bit of a beast to tame, I found that we didn't actually have to jump through some of the hoops we did in the last video to find the variance. So look at this. I thought that we might just be able to go tf.reduce variance. It turns out we can find the variance of our tensor in a very similar way than what we've done here, finding the standard deviation, which is strange because with these methods, you can get rid of the math, but with the variance and standard deviation, you require the math. And so we've both learned something here. So I want to just show you here, if we want to go find the variance of our E tensor, we go tf.math.reduce variance E, just exactly like we've done here in the documentation. And if you're ever stuck, you can just go through the documentation here, like tf.something, and just read up all the different methods. I mean, we're working with tf.math, so you might want to even try a fair few of these just to see what happens with what you're working on. But anyway, let's go back here. We'll find the variance. Input must be real or complex. How did we fix that? We'll go tf.cast. Let's change this dtype to tf float32. And, oh, we forgot a little bracket on the end. Wonderful. We get a very similar number up here to our variance that we found using the TensorFlow probability. So, turns out we actually don't need access to TensorFlow probability. However, what we just went through was a great exercise in figuring things out. I mean, at first you'll try something and it might not work, and then you'll find a fix to it. Then you'll find that, hey, the fix probably wasn't even the best way of doing it. We did a little bit more research and we found we wanted to find the variance without inputting any other libraries aside from TensorFlow. We can just do it like this. But anyway, let's get into finding the positional maximum and minimum. Now, when might this be helpful? Well, you're going to see this a lot when your neural network outputs prediction probabilities, which we haven't seen yet. But if we go here, so remember our little example where we got our images, we input it into some numerical encoding, goes through our neural network, finds the patterns in there, adjusts its random weights that it initializes with, it updates its representation outputs. And then here, oftentimes the representation outputs are referred to as prediction probabilities. So in this case, 983 is the highest number, 0.04, 0.013. So imagine if above here, if this column was, say, ramen, and this column was, say, spaghetti, and this column was, say, not ramen or spaghetti. So in this case, this number, the highest output, this is our ramen column, would be dedicated to ramen because the first index here, the 0th index, the highest number goes to ramen. And then if we wanted to turn this row into labels, we might go ramen, spaghetti, not ramen or spaghetti. Which one has the highest value? The index where spaghetti occurs. And then for this one, which is no food, so ramen, spaghetti, no food or spaghetti, this is the highest number. So we might want to get this index. So that's what I mean by finding the positional maximum minimum. At which index of the tensor or of this row does the maximum value occur? So in this row, it occurs at the 0th index. In this row, it occurs at the first index. And in this row, it occurs at the second index. But let's have a look how we might do that in code. So the first thing we're going to do is create a new tensor. So create a new tensor for finding positional minimum and maximum. We go here, f equals tf random. We'll create a random tensor with uniform this time. We'll give it a shape of, we'll get it 50 long. Let's have a look. Beautiful. Now I wonder if we go here, tf random set seed equals 42. Do we get the same numbers? So this one is, you help me remember what's this first number, 6645621. Okay, beautiful. So if you use random seed 42, you should get the same numbers as me. Don't worry too much if you don't, if something's changed between now and when you watch this video, but we just need a tensor with 50 random numbers and we can work with this. So if we wanted to find the maximum element position of f, meaning at which index does the maximum value occur? So I'm going to guess, let's have a quick look. There's 948. Can we beat that? Yes, we can. There's 967. So that'll be about, maybe 43. Let's try. TF. So find the positional maximum. Now, the positional maximum is often referred to as Argmax. So I believe it's the same in NumPy, mp.argmax. If we wanted to find the docstring here, returns the indices of the maximum values along an axis. Same with Argmax. Returns the index with the largest value across axes of a tensor. So let's do it. Let's put in our 42. Oh, so we were close. Now, if we were to index on our largest value position. So what I mean by this is if we grab our F tensor and then we find Argmax F, what value are we going to get? Boom, it's that value there. And then if we go find the max value of F, tf.reduce max F. Do all these values line up? Wonderful. So this should, now let's check for equality just to be safe. If we go Argmax TF, Argmax F, does this equal? We might put a little assert here because this will error if they don't equal. No error. And then if we take away this assert, we should get true. Beautiful. So this is where indexing. Does this make sense that they are equal? Because look, we found the positional maximum, which gives us position at index 42, which is this one. That's the maximum value of this tensor. And then we can index on our largest value position. So it's saying, hey, take the F tensor and grab position 42, or grab the value from position 42, which is this. Yes. Now, if we use just our reduce max method, which is saying, hey, find me the max value of F, we get this value, and then we check to see if they're equal. Beautiful. Now, another one you might use, I don't use this one as often, is finding the minimum. So wherever the positional minimum occurs in here, can we find it? There's 0.03, that's pretty low. So maybe it's that one. Or there's 0.009. So I'm guessing that might be at, let's go 21 or 20. So find the positional minimum. We want to do TF, you might be able to, if Argmax finds the maximum, what do you think finds the minimum? If you guessed Argmin, 100 points for you. Boom, so position 16, let's find out what it is. Find the minimum using the positional minimum index. So F, TF, Argmin, F. 0.009, so that was actually 16. There we go, so that's index 16. Beautiful. Alrighty then. So what we might do in the next video is we can see how we can squeeze our tensor. In other words, removing all single dimensions. So have a go at this. Maybe create your own tensor. Can be as big as you like. And practice around using the Argmax and Argmin methods to see if you can find the minimum, maximum positional values of your tensor. And I'll see you in the next video. How'd you go? Did you create your own tensor? Did you find the minimum and maximum positions? I hope you did. But for now, we are on to the next part, which is squeezing a tensor. Oh, we're going to give our tensors a big hug. In other words, removing all single dimensions. You're going to fall in love with tensors by the end of this course if you haven't already. Now, what we might do is, as always, we need to create a tensor to get started. Now, I might go here, G. Are we up to G? Yeah. E, F, G, H, I, J, K, Elemental P. I won't do that again. No promises, but I like to sing. Now, if we go here, what have we got? So I'm creating a similar tensor to what we did before, random uniform, but in this time, we're going to use the shape parameter to add a few single dimensions right to the start. So if we check G, look at this. So we have just, actually, let me use our faithful random seed as 42. Beautiful, we're getting the same numbers there. Yep, 6645, 621. Maybe I'll know that off by heart by the end of this course. And so we have here, the shape is what we have to pay attention to with squeezing. So this is shape 11150. So see here, we've got a few square brackets, 1, 2, 3, 4, and then the innermost square brackets is where the big dog 50 is sitting. Now, what we're going to do with squeezing, it's actually quite a fun little concept. So if we go G shape, we get that. Now, if we were to go G squeezed, that could be our TensorFlow wrapper name, G squeezed. TF squeeze, and now, actually, we'll check the docstring. Removes dimensions of size 1 from the shape of a tensor. Now, if I were to run this, what do you think G squeeze new shape is going to be? I'll give you 3, 2, 1 to guess, and now let's check. Boom. So there we go. So what squeeze does is, we just read that before with the docstring, but we'll read it again. Removes dimensions of size 1 from the shape of a tensor. So if your tensor has too many single dimensions and you want to just reduce it, so get rid of all these extra dimensions here and reduce it back to its essence, you can use the squeeze method. So that's a little tidbit there. Nice and quick video, this one. And the next one, we're going to cover one-hot encoding. So I'll see you there. Okay, so if you wanted to one-hot encoding tensors. Now, what is one-hot encoding? Let's check this out. What is one-hot encoding? If you've done any machine learning before, you might have come across one-hot encoding, but it's a very important concept in terms of preparing data. This is a great website, by the way, Machine Learning Mastery. So let's check what this says. There, okay. So this is a great example. We'll create our own in a minute, but let's just have a look here. So we've got 3 columns, red, green, blue. So row 2 has a 1 for red and 0 for the rest. So that is one-hot encoded for red. Row 3 has a 1 for green, but 0 for red and blue. So that is a one-hot encoding for green. And row 4 has a 0 for red, a 0 for green, and a 1 for blue. So that's a one-hot encode for blue. So that's a great way to turn, if we just remember, what do we have to do when we're passing our data to neural networks? We have to find a way to numerically encode it. One-hot encoding is a form of numerical encoding. So if we had the colors red, green, blue, and we wanted to pass it to our neural network, it would look at that and go, you know what? I'm very smart. I can find out patterns and numbers, but when you pass me words, red, green, blue, I can't understand them. So we could one-hot encode those words. Red could be 1 for red, 0 for blue, 0 for green, and so on, and then pass those as a tensor to our neural network. So let's have a look how we might do that in code. What we should do is create a list of indices. So values, pretend this is, let's get our sum list. Sum list can be 0, 1, 2, 3. In other words, maybe we go, could be red, green, blue, purple. And now, if we wanted to one-hot encode this, we can go one-hot encode our list of indices is tf.1hot sum list. We're missing one positional argument. All right, let's look up the docstring. What does this say? tf1hot returns a 1-hot tensor. If on value is not provided, it will default to a value of 1 with type dtype. Okay, where's the example? Here we go. For example, indices equals that, depth equals 3. We need to pass a depth parameter. Okay, so the output's going to be 3 pi 3 because this is 3 long and the depth is 3. So let's figure this out. Depth. If we have 4 elements here, what I've kind of given it away here, so pretend you can't see that. Well, it's going to be 4. Let's try it out. There we go. So do you see what's happened here? What kind of tensor we've created? We've transformed this tensor, some list, into one hot encoded version of itself. So for the first row, this relates to the first element. So it's got a 1, as you see, for where 0 occurs, but then 0 for all of the other values. And now for this one, we've got this refers to this value here. It's got 0, yes, and a 1 because this is a number 1 here, and then so on for the other 2 values for each rows. Beautiful. Now, a fun little thing that we can do is that if we wanted to change this from, I mean, you're rarely going to use this in practice, but I want to show you anyway because it's cool. If you wanted to show, get rid of, rather than using 1s and 0s, we can use on value and off value and pass them different values. So let's go specify custom values for 1-hot encoding. If we want to do tf1hot, sum list, depth can be 4, and then on value can be, yo, I love deep learning. And then the off value can be, let's go, what could we do? I need something fun here. I also like to dance. Boom. Let's see what this comes out with. Oh, yo, I love deep learning. I also like to dance. 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 Yo, I love deep learning. I also like to dance. Did you know I like to dance? So have a practice with tf1hot. Maybe create some of your own on values, off values. Again, rarely will you ever use them when you're passing them to a neural network because a neural network, what does it love? It loves numbers. But yeah, this is just a little fun exercise to practice 1-hot encoding. Now, if we look up the tf.1hot, I believe it requires, so the indices, the indices have to be a tensor of indices. Okay, well, that makes sense. So yeah, go through the example there, create your own list of indices, and then 1-hot encode it, practice around, see what happens if you change the depth parameter, and then change the on value and the off value. And I'll see you in the next video. Did you have some fun creating 1-hot encoded tensors with different on and off values? I hope you did, and I hope you're loving deep learning. We actually haven't covered too much deep learning yet. We're still in the fundamentals, but I do believe you do like to dance. So by the end of this section, you're going to be able to dance through your way through TensorFlow code. And speaking of which, let's do a little bit more dancing through, there are some math functions. I just want to show you how to use a few more of these that you may come across. There's a lot here, as you see, tf.math overview. We've got a whole bunch here, but let's practice with a few more. We can never get enough practice. We might go a few common mathematical operations, a squaring, log, and square root. So let's see how we'll do that. First things first, let's create a new tensor. So this time we might go h, I believe we're up to. So tf, I'm going to show you a new way to create a tensor. 1 to 10. Nice and simple. Oh, let's see it. There we go. Now, if we want to square it, how do you think we might do it? TF square H. Beautiful. So we get just the square of all that. So 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, etc., etc. And then if we wanted to find the square root, let's find the square root. We come over here. Maybe we go square root. Will this show us? There we go, tf math square root. Beautiful, let's try that. Now I believe it may have an alias. We can just skip the math part. Oh, what do we got here? Invalid argument error. Value for attribute t of int32 is not on the list of allowed values. Okay, this is good. So again, we're coming across a value error where it's saying that int32 is that the type of our tensor? Yes, it is. Int32 is not in the list of allowed values for this function. So we want b float, half float, double, complex 64, complex 128. Okay, let's change it into a float. tf.Cast. And the dtype is going to be tf.Float32. Oh, forgot again. Boom! Look at that. There we go. Actually, let me put this one above here so that you'll know for future reference is that this is going to be will error. Method requires non-int type. So if we put here just h, we get an error. Wonderful. How about we find the log? So we go here, find the log. Now, again, TensorFlow, oops. We want to go up here and search for log. tf math log, wonderful. Computes the natural logarithm of x element-wise. Has it got an alias? I'm pretty sure we can skip the math part, but if not, we can try it out. So find the log, tf log of h. Has no attribute log. Oh, do we need math for this one? We do. Oh, again, we get the same error as above. So what do we have to do here? Value for t of int32 is not on the list of allowed values. What do we have to do? I'll give you a hint. We have to turn it into a float, or at least one of the allowed values. We've got some rules here. So we go here, tf.Cast h dtype equals tf.Float32. Will this work? Wonderful. There we go. So that's just an example again of how many different functions you're going to find in TensorFlow, and a little bit of practice again, as I can't stress this enough, is how much practice we're going to need sort of just making sure our tensors are in the right data type. So have a play around with some of the functions in tf.math and see how many of them, pick 3 and try them out. The ones that we haven't covered so far, and see if you come up against any errors like this, what you can do to fix them. So that's a little challenge before the next video. We've covered a whole bunch so far, and we've even seen before how tensors can interact with NumPy arrays. But let's have a dedicated session on tensors and NumPy. So if you've done any numerical computing before or any type of data science or machine learning, you've probably used NumPy. So if we come here, what is NumPy? Not going to dig too much into this because we want to get focused on using it. But chances are, there we go, the fundamental package for scientific computing with Python. So NumPy is a fundamental library for any type of numerical computing with Python, and it's all built upon the NumPy array. So TensorFlow interacts beautifully with NumPy arrays. And we can see an example of that by, if we create a tensor, this is what we've seen before, directly from a NumPy array. So if TensorFlow is built upon the tensor, NumPy is built upon the array, and the beautiful thing is that they basically have full interoperability. I believe that's a word. That's like a fancy word for they work together quite nicely. So there we go. We create an array here, and then we pass it to tf.constant to turn it into a tf.tensor. Beautiful. And now we can convert it back from a TF tensor to a NumPy array. So convert our tensor back to a NumPy array by just going np array j. And then we can check the type here by going type np array j. There we go. So np array j turns it into a NumPy array, and then when we check the type, it turns into an numpy.nd array, which is NumPy's base type, just like TensorFlow's base type is tf.Tensor. All right, and we can also do the same thing as the cell above by convert tensor j to a NumPy array using, if we go j.numpy, we've also seen the NumPy method in Tensor before as well, .numpy, and then if we check the type, j.numpy, we go here. Beautiful. So we can convert it back to a NumPy array there. Now, where this might be helpful is sometimes if you have, say if we have, let's rewrite j to be tf.Constant. It's just a single number there. If we wanted to have access it just as the float on its own, we can actually do .numpy. And there we go. That'll give us access to it there. And if we want to go there. So the beautiful thing about being able to really easily convert our tensors to NumPy arrays and NumPy arrays into tensors is that if there's some sort of functionality that we want to use with that doesn't work with our data in tensor types, we can convert it to a NumPy array and use it there, and vice versa. So if we delete that, let's see, there's one more thing you should know, and that's default types of each are slightly different. So if we want to create numpyj equals tf.Constant. We'll create this directly from a NumPy array, just as we've done before. It's going to go np array, same as above, 3, 7, 10. Wonderful. And then if we want to go tensorj equals just tf.Constant, we'll create this one directly from a Python list, 3, 7, 10. Now, if we want to go check the data types of each, now we've had some practice doing this, so you might be able to know if we wanted to check the data types of numpyj and tensorj, what might we use? If you guessed we use the dtype attribute, you'd be 100% correct, tensorj. And if you didn't guess correct, well, that's all right, we get to practice. Boom. So there we go. So if we create a tensor from a NumPy array, the default type is float64, whereas if we create a tensor from a Python list or directly through TensorFlow, the default type is going to be float32. Now, the reason why this is important is because, remember, we actually had some errors up here where we had to change the type of our tensors from a certain data type to another data type. So this is where I want you to be aware is that if you do convert your NumPy arrays into tensors, they may have a different data type compared to if you created your tensors directly from TensorFlow. So just be aware of that. One of the main issues you'll run into when computing with different tensors is different data type issues. So treat this as your heads up. But that's a quick reiteration of tensors and NumPy. Remember, NumPy is a fundamental package for scientific computing with Python, and chances are, when you're doing machine learning and deep learning, you're going to run into NumPy somewhere. So keep in mind, TensorFlow works beautifully with NumPy arrays and vice versa. In the last video, we checked out how beautifully TensorFlow interacts with NumPy, and I kind of just added a little tidbit here. Remember the key emoji? If I've picked up a little tidbit that you should be aware of, I'm going to include it here with this little emoji as a key. Get it? There's a key there because it's a key idea. Anyway, you might be wondering, why are we using differences like NumPy arrays and tensors look basically the same when they come out? I mean, if we print one of our tensors, we get the NumPy version of it at the end. Well, one of the main differences between a TensorFlow tensor and a NumPy array is that a TensorFlow tensor can be run on a GPU or TPU for faster numerical processing. So remember, if we look up a GPU, it's a graphics processing unit. There we go. A graphics processing unit is a specialized electronic circuit designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer intended to output to a display device. Oh my goodness. In other words, they're really fast at doing numerical computing. And then we also have a TPU, which is a tensor processing unit. So a tensor processing unit is an AI accelerator, application-specific integrated circuit ASIC developed by Google, specifically for neural network machine learning, particularly using Google's own TensorFlow software, which is what we're getting familiar with right now. How exciting. So if we come down here, this is what this lecture is all about. That was kind of a long-winded intro to how you can find access to GPUs. Boom. So if we wanted to use our tensors on a GPU, how might we do that? The whole time we've been connected to Colab, and if we look here, it says connected to Python 3, Google Compute Engine backend, RAM, disk. I wonder if, how might we, let's go TensorFlow, check GPU usage. Let's see this. tf.test is GPU available. That makes sense. Returns whether TensorFlow can access a GPU. Deprecated. What is it? Where is it? Have we got config here? What if we search? I believe it's called list physical devices. Oh, what happened there? TF config. There we go. List physical devices. Return a list of physical devices visible to the host runtime. This is how we're going to check what type of device TensorFlow is running on. So tf config list physical devices, we could type that out, but I'm going to write that in. tf.config list physical devices. Does that need, is that a method? What comes out here? Okay, physical device name, CPU, device type, CPU. So right now, we're running on a CPU. So this is a central processing unit. Now, this is also a computer chip, very fast at doing numerical computing, but not as fast as a tensor processing unit or a GPU. I'll let you do your research in terms of comparison between CPU and GPU for numerical processing, but just for now, trust me, GPU and TPUs are much faster than CPUs, and we'll see this when we start to write neural network code. However, if we wanted to, we can actually pass GPU to this. It says none. So it's going to return a list of the physical devices available. And right now we have no access. So you might have seen this in the Introduction to Colab video, but if not, I'll show you how we can get free access to a GPU, which is beautiful on behalf of Google. So if we go change runtime type, now I'll just redo that again. Runtime, change runtime type. Oh, what does this little question mark say? More info. GPU availability. Let me zoom in here. What types of GPUs are available in Colab? The types of GPUs that are available in Colab vary over time. This is necessary for Colab to provide access to these resources for free. Oh, that is exciting. That means we get access to a GPU for free. So thank you very much to Google. The GPUs available in Colab often include NVIDIA K80s, T4s, P4s, and P100s. I'll let you check out which ones are, what the differences between those are. Essentially, the higher the number, the faster the GPU. So this one's the fastest. T4 is faster than the K. These are actually in order in terms of speed. So I believe K80 is still very fast compared to a CPU, but not as fast as a P100. There's no way to choose what type of GPU you want. But anyway, you can keep reading that. If I want to change the hardware accelerator, it starts off as none. So whenever you start a default Colab notebook, you're going to get no GPU. So Google can allocate, compute power isn't free. So if we want to use a hardware accelerator, we have to choose. We can choose a TPU if we want, which is even faster than GPU, but that requires a little bit more setup. For this course, we're going to be focused on GPU. If you want to learn how to use a TPU, there's a great TensorFlow guide on that. I'll let you research that in your own time. Anyway, we'll go to GPU. We're going to click Save. then our runtime is going to actually reset. So if we wanted to run this cell, because our runtime reset, we don't have access to TensorFlow anymore. But that's all right. So if we go here, import TensorFlow as TF and run this, there we go. It shows that now we have a CPU and a GPU. That's what we're after. So if we go in here, just type in GPU. Wonderful. And we can also check it because it's using an NVIDIA GPU. We can use this little command here, which is called bang, to basically say run this on the command line. We're going to type in NVIDIA SMI. I'm not quite sure what SMI stands for. If you want to tell me in a message, that'd be phenomenal. But I just know that this is the command to check what type of GPU you're using. Wonderful. So we've got access to a Tesla T4 GPU with almost 16 gigabytes of memory, which is this is actually quite a fast GPU. We're not going to take full advantage of it just yet. It's running CUDA version 10.1, which is basically, we look up CUDA, basically a driver, Compute Unified Device Architecture, which is a driver that is a parallel computing platform and application programming interface API model created by NVIDIA. You can read the full Wikipedia article if you want. What it does is it's kind of the interface between the GPU and our TensorFlow code that makes our TensorFlow code run really, really fast. And so, one last note, this is actually probably going to be the last video of this TensorFlow fundamentals section. The note here and the important takeaway is you might be wondering, okay, I've set up access to a GPU. Now, how do I get my TensorFlow code to run on it? Well, the amazing thing is, if you have access to a CUDA-enabled GPU, and in our case, since we're using Colab and we do have a CUDA-enabled GPU, well, guess what? TensorFlow will automatically use it whenever possible. So we haven't actually done anything too intensive in terms of finding patterns in data using our neural networks. But to find patterns in data, to discover what's in an image and create representation outputs like this, our neural network algorithms are going to have to do a lot of mathematical calculations. And we're going to be writing TensorFlow code to do those calculations. And the beautiful thing is, because we have access to Google Colab and a GPU, those calculations are going to be sped up as much as possible. So let's have a quick just overview of what we've covered. We started with Introduction to Tensors. We learned a whole bunch of different ways to create tensors. We figured out how to shuffle the elements of tensors. We even made tensors with other ways, with TF1s, TF0s. We learned about NumPy and NumPy arrays in tensors. We actually covered that twice because it's such a fundamental concept. We figured out how to get information from our tensors, index them, change the data type, aggregate them, find the positional max and minimum, squeeze them, one-hot encode them, square, log, and square root. And again, how to make our calculations extremely fast by having free access to GPU with Google Colab. Now, with that being said, we have a whole bunch of different tabs here. Although we've covered a whole bunch, we've barely scratched the surface of the TensorFlow library. I mean, you can look at it here. Look at that. There's too much here to cover in a single course. So there are, well, actually, the good news is we've covered the fundamentals, the building blocks of what you'll need to sort of start your journey with TensorFlow. We've probably actually done a little bit more than that. But anyway, there's going to be a couple of exercises in the upcoming video, as well as some extra curriculum, mainly being just getting familiar with the TensorFlow documentation and trying out a few different things. So check out that lecture resource there. Go back through the material to solve those exercises, and I'll see you in the next section. But congratulations for getting familiar with TensorFlow. Give yourself a pat on the back. You have now passed the TensorFlow fundamentals section. Woohoo! Welcome to Neural Network Regression with TensorFlow. Now, we've seen some of the basics of TensorFlow in the previous section. Now we're going to get hands-on building some neural networks with TensorFlow, specifically neural networks for regression. Now, before we get into things, I'm going to start this lesson off with a slide called Where Can You Get Help? Now, this is very important because learning a new concept is challenging, of course. So, that being said, if you do get stuck, here are the steps I want you to take. First of all, follow along with the code. I'm going to be writing it with you. Remember our motto, if in doubt, run the code. If I'm going too fast, that's all right. Slow the video down, then try it for yourself. If I'm going too slow, you can speed the video up and beat me. If we're writing TensorFlow code, don't forget in Google Colab, you can press Shift Command Space to read the docstring. That will get you a little bit of information about any of the functions that we're running. And then, if you're still stuck there, if the docstring doesn't have that great of an explanation, remember, most docstrings in TensorFlow have examples of different code, so try it for yourself. But then, still stuck, search for it. You're going to become very familiar with these two resources here, Stack Overflow, and of course, the TensorFlow documentation, which is forever improving, forever getting better. So it's very vast, but with a lot of experience, hands-on practicing, checking it out, you'll start to get much more familiar with it. Then, once you've learned some things from searching for it, don't forget to try the code again. Remember, back to the motto, if in doubt, run the code. You can't break anything. And finally, if you're still stuck, ask a question. I'm going to emphasize here, including I'm putting inverted commas. You can't see my face in this video, but I'm doing the inverted commas symbol with my fingers. The dumb questions. Don't forget the Discord chat. Ask a question if you're stuck. Very important skill to have is asking the right question. Now, with that being said, if we're going to do neural network regression with TensorFlow, you might be thinking, what is a regression problem? So let's have a look at a couple of examples of what regression problems are. Here we go. Some example regression problems. Say we're trying to predict the house or the sale price of a house we're interested in. So how much will this house sell for? If we've got a house down the street and we want to try and predict how much it's going to sell for, we might ask ourselves, how much will this house sell for? We just said that, didn't we? Another regression type problem is, how many people will buy this app? Or how much will my health insurance be? Or how much should I save each week for fuel? Now you'll notice a trend here with these questions. It's how much or how many. That's one of the key points of a regression problem. It's predicting a number of some sort. And if you're thinking about in terms of price or numbers in these types of questions, well, there are other types of problems where a regression, we can turn them into a regression problem, such as trying to predict the coordinates of where the boxes should be in an object detection problem. So these are numbers here. So say we've got 1390, so that would be on the x-axis. This corner, the top left corner of this particular box here, should be at 13 pixels in, but 90 pixels down, and so on for the top right corner, the bottom right corner, and the bottom left corner. And then again, we could do the same with these corners here, the top left. Remember, this is the perpetrator who hit and run on my car. So if I was going to build an object detection model to look at security footage around my home to see if I can find the people who hit and run on my car, I might train an object detection model, specifically a neural network regression, to try and predict the corners of where the bounding box should be around my target object. So this is what I want you to start thinking about. Although we have a kind of a one-liner definition for regression problems, predicting a number, is that a lot of the time in machine learning and deep learning, how you sort of think about the problem will definitely define how you approach that problem. And again, if you're not satisfied with the definitions here, this is what we can do. So what is a regression problem? Regression analysis. Here we go. In statistical modeling, regression analysis is a set of statistical processes for estimating the relationship between a dependent variable, often called the outcome variable, or one or more independent variables, often called predictors, covariates, or features. Okay, so we want to predict the relationship. So say this line, that's the relationship there. So the dependent variable, in our example problem of trying to predict the house price, our dependent variable might be the price of the house. So the house price is the outcome we're trying to predict. And the independent variables, often called predictors, covariates, or features, might be the number of rooms in the house, or the number of bathrooms, or the number of garage spaces, or all three of those combined. So the independent variables, so we might have 10 different houses with 10 different numbers of bedrooms, 10 different numbers of bathrooms, and 10 different numbers of garages, and 10 different house prices. And we might want to build a model to take in all that information and then predict what the house price might be. So with that being said, we're going to get into more examples of this later on as we write code. But let's have a look at what we're going to cover. Broadly, of course, we're going to be writing lots of code to do these things. We're going to cover the architecture of a neural network regression model, so specifically the building blocks of a neural network regression model, the input shapes and output shapes of a regression model, in other words, the features and labels, or, in Wikipedia terms, the dependent variables and the independent variables. We're going to look at how we can create custom data to view and fit. We're going to take care of the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. If all of these don't make sense right now, don't worry. We're going to get very hands-on with them and they'll start to make sense as we code them. We're going to look at different evaluation methods for regression models. And finally, we're going to look at how we can save and load our models so that if we do train a machine learning model and we save it, we don't have to go through that process of retraining. And if we want to load it into our applications going forward, we can do that using our save and load methods. And finally, how are we going to do this? A big emphasis between the chef and the chemist. Chemist is very exact, whereas what's a cook do? A cook tries things out, a cook experiments, pours in little bits of different flavoring. We're going to be cooking up lots of code. So with that being said, here's what we're going to cover. In the next video, let's have a look at what the inputs and outputs of a regression problem or neural network might look like. So if we're dealing with regression problems, well, we're trying to build neural networks to solve regression problems, what might be our inputs and outputs? Remember, in machine learning and deep learning, a lot of the time your focus will be on defining your inputs of your algorithm and what the outputs of your algorithm look like. So let's say we wanted to predict the sale price of this house. Now, this is an actual house that was up the road from me, not far from where I live, that was up for sale. And say I wanted to build a machine learning model to try and predict what I should offer if I was going to auction what this house should sell for. So again, here's our little diagram of what we're going to be focused on. We have the inputs. So what might our inputs be if we're trying to predict what our house might sell for? And what might the outputs be? So if we're just looking at this diagram, and if we want to build a machine learning algorithm, we might have to build this ourselves. But first, let's focus on the inputs and outputs. So maybe we've got our house, and we know a few things about it. The number of bedrooms, the number of bathrooms, and the number of garages that it has. And we might have a whole bunch of other houses that are nearby, and we know what their sale prices are. What might we do with that? So we know these, okay. If we come back to our definition of a regression problem here, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. Okay. So in our case, our independent variables might be the number of bedrooms, 4, the number of bathrooms, 2, and the number of garages, 2 as well. So for our machine learning model or deep learning algorithm, we're going to have to encode these in some numerical way because we can't just pass 4 bedrooms, 2 bathrooms, 2 car spots. So we'll put them into a numerical encoding, and as you might see here, this is a one-hot encoded. We've seen this before in the TensorFlow basics section. And so if we had this array here, or this tensor, this vector could be number of bedrooms. So it's 0, 0, 0, 1. Now what that would mean is that, does it have 1 bedroom? No. Does it have 2 bedroom? No. Does it have 3 bedrooms? No. Does it have 4? Yes. So we put a 1 there. And in this case, does it have 1 bathroom? No. Does it have 2 bathrooms? Yes. Does it have 1 garage? Yes. So 0 in case of one hot encoding encodes for not that thing, and 1 encodes for that thing. So that might be our numerical encoding. Wonderful. We put these into here, and that's our inputs to our machine learning model. And these are often called input features, or in Wikipedia terms, predictors, covariates, or features. So features is probably the most dominant term that I use in practice and we're going to use throughout this course. If you ever hear input features, it's some kind of information about the data we're using that goes into our machine learning algorithm. And so in our case, if we want to put our inputs into a machine learning algorithm, so often one, and you'll find this in deep learning a lot, is that often an algorithm for your problem already exists. So that means someone has built something that has worked before for their problem, might be very similar to your problem, and you can utilize that for whatever you're working on. However, if it doesn't already exist, we can see how we can build our own. That's what we're going to be practicing. We'll see how we can build our own. But later on in the course, we're going to see how we can use algorithms that already exist. And finally, if we have a look at what our outputs might be, we might, if we're trying to predict the sale price of this house here, based on the fact that it has 4 bedrooms, 2 bathrooms, 2 car spots, and it's on a pretty big piece of land, if we wanted to make an offer, we're using our algorithm to figure out how much we should offer at auction. Our algorithm's telling us we should offer $939,700. Now, where does it get this predicted output from? If we have a look at what it actually would sell for, $940,000. So we weren't too far off here. We'll figure out some evaluation metrics to compare predicted outputs of our deep learning models to the actual outputs of what they should be, for regression problems, that is. Now, this predicted output comes from looking at lots of these actual outputs. So remember how we talked about supervised learning? Well, this is an example of supervised learning. So we might have 100 or 1,000 or tens of thousands of different homes with all of their input features and their actual sale price. And then we might feed these inputs and outputs to our machine learning algorithm, and it's going to learn the relationships. Remember, we come back to our definition of a regression problem. Regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, right, so our sale prices, and one or more independent variables, so our input features here. So after our machine learning algorithm has looked at many, many examples, comes from looking at lots of these, of input features and outputs of house sale prices, it's going to learn the relationships between the input features and the outputs here. And then for use cases where we would like to predict the potential output of a home that we don't know the actual sale price for, we can feed its input features into our algorithm and have a suggested output of what the sale price or what we should pay if we were going to auction. So this is just an example of what regression inputs and outputs look like. We're going to have some practice writing code to do this very shortly. So another big point is once we've defined our inputs and outputs, and I can't emphasize this enough, is this is what we'll be focused on a lot of the time in machine learning and deep learning, is the blue parts here, defining our inputs, defining our outputs. And now another key term is when we're talking about inputs and outputs, is input and output shapes. So say here, we were taking our input features, numerically encoding them, feeding them to our machine learning model as inputs. Our machine learning algorithm works out the patterns or utilizes its already learned patterns to produce an output, aka the sale price of our home. What might be the shape of our inputs? Because remember, our numerical encoding is going to be in the form of a tensor, and this output here doesn't look like it, but it will also be in the form of a tensor. So here we go here. We've got bedroom, bathroom, garage represented as a tensor. And in this case, the shape is going to be 3 because we've got 3 input vectors here. Now, don't be confused by this outer bracket here. Because we've got 3 input features, the shape of our input layer to our machine learning model is going to be 3. 1 for bedroom, 1 for bathroom, and 1 for garage. We'll represent this as a tensor. And for our outputs in our regression problem, in this case, can you guess the shape? Is going to be 1. So in our case, for each example that we're going to pass through our machine learning algorithm, each sample will have an input shape of 3. So we need number of bedrooms, number of bathrooms, number of garages. And each sample will have an output shape of 1 for the price of what we're trying to predict. And now this is just for our housing price prediction example. We can adjust these. So here, the bedroom, bathroom, garage, to be almost as many different inputs as we want. But usually for a regression problem, the output shape is often 1 because we're trying to predict some sort of number. So again, if we come back to Wikipedia terms, we're trying to figure out the relationships between a dependent variable, often called the outcome variable, and one or more independent variables. So in our case, these are our independent variables, and this is our outcome variable, or our dependent variable. Now, with that being said, we've covered inputs and outputs of our regression problem. Let's now have a look at what that might look like in terms of building or writing neural network code. We'll have a look at it in the concept of an architecture of a neural network regression model. Recall in a previous section that we covered the anatomy of neural networks. So essentially every neural network that you build will have an input layer, some number of hidden layers, and an output layer. And for your input layer, this is where your data goes in. Now, hidden layers is plural on purpose or optional plural. It can have 1 up to 100. Some neural networks even have 1,000 hidden layers. It really depends on what problem you're working on. And now that's where the deep and deep learning comes from. So if you imagine if we had 10 of these hidden layers laid out here, or the more we had, the deeper our deep neural network would be. And then for the output layer, this is where the outputs or the learned representation or prediction probabilities of your neural network come. And within the hidden layers is often where your neural network is learning patterns or weights in the data. And so keeping this in mind, if we have an input layer, a hidden layer, and an output layer, what might the architecture of a neural network regression algorithm look like if we wanted to build one with TensorFlow? So this is what the typical architecture of a regression model in TensorFlow will look like. So in our case, we have a few hyperparameters here. Remember, a hyperparameter is a setting that you as a data analyst or a machine learning engineer can change. So we might have the input layer shape, the hidden layers, the neurons per hidden layer, output layer shape, hidden activation, we haven't covered that yet, the output activation, the loss function, and the optimizer. Now we haven't covered the bottom half of this little graph here, but that's okay. We're going to get very familiar with that as we write code. And now I just want to emphasize that I've adapted this from page 293 of the Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow, book by Aurélien Guérin, which is a phenomenal book. This is probably going to be my #1 external resource to go along with this course, is this book. I've read it end to end in its entirety, and I'd highly recommend it if you're looking at learning more with TensorFlow. But that's beside the point. We're getting hands-on here. Now, in terms of the typical value for each of these, the input layer shape, we've covered this a little bit before. So if we were trying to predict the sale prices of different houses, we might have an input layer shape as the same as the number of input features that we have. E.g. would be 3 for number of bedrooms, bathrooms, and car spaces in housing price prediction. Hidden layers, the value you have here is very problem specific. The minimum is 1, the maximum is unlimited. Again, the neurons per hidden layer is going to be problem specific again. So if we come back to our anatomy of neural networks, so this has 3 hidden neurons. So not only can you customize how many of these layers that you have, you can customize how many of these little circles here, also referred to as neurons. So you could have 100 neurons here times 100 layers, and that would be a very deep model. Now, the output layer shape, This is the same for the desired prediction shape. For example, 1 for our housing price prediction problem. Hidden activation is usually ReLU, which is rectified linear unit. Output activation, this is going to be problem specific, but these are some typical values here. The loss function for a regression model is, the default one is usually mean squared error or mean absolute error / Huber loss, so which is a combination of mean absolute and mean squared error. If you have outliers in your data, again, we haven't covered these four here. We're going to see what they mean shortly. And then the optimizer, which is a way of how our neural network improves its predictions, is usually going to be stochastic. Oh, that's a fun word to say. Stochastic gradient descent. Stochastic is a fancy word for random. Or the atom optimizer, which is a very good default value. So let's have a look here what this looks like in TensorFlow code. We haven't written any of this, so don't worry if it feels foreign to you. We're going to write a lot of this going forward, but I just want to relate the architecture of a regression model, see what we're going to start working towards. By the end of this module that we're covering, this section, you're going to be able to write these yourself. So let's have a look. This is the input layer. So the input layer is in the blue, so we see the shape is defined here as 3 because we're working with our housing price prediction. The hidden layers is in this other little blue shade here. So these are known as hidden layers. So we've got an input here and then an output here. Remember, all neural networks have some sort of input, some sort of output. Then the hidden layers, in our case, we have 1, 2, 3. And if we look for the neurons per hidden layer, is often this first number. So we have it in green. In our case, we've got 100 neurons in the first hidden layer. We've got 100 neurons in the second hidden layer. And again, the same for the third hidden layer. Now our output layer shape, we can see here in the yellow. This is the same shape as our desired prediction shape. In our case, this would be a great output shape for our housing price prediction. Then we have the hidden activation parameter. In our case, it's the ReLU, which is a rectified linear unit. So that we can set that using the activation parameter. And then for our output activation, which is just simply the output activation function for our output layer, we've decided to set this one as none. And then for our loss function, if we come down here, we've got step 2, which is compiling a model. So this is step 1 is we created a model. Step 2 is we have to compile it in TensorFlow. Again, we're going to be writing a lot of this code going forward. So we define our loss function. This measures how wrong our neural network's predictions are. So when it's learning the relationships between our independent variables and our dependent variables, in other words, the number of bedrooms, bathrooms, and car spaces, and the sale prices of our homes. This loss function is going to measure how wrong our neural network's relationships are. And the optimizer here, in our case, we've set it to, which is in the black square here, we've set it to the atom optimizer, is going to inform our neural network how it should improve our patterns to reduce the loss function. So again, if we look at this in the context of our housing price prediction problem, we see we have the input features here, which is going to go into our input shape. They'll pass through the hidden layers, which will learn the patterns between the input features and the output variable. And then it's going to come out into our output layer, which is going to output something like this. And then the loss function is going to tell us, or tell our neural network, how wrong the relationships between these and this is. And then the optimizer will tell our neural network how to improve the patterns it's learning between the input variables and the output variable. And then here, the fit model is telling our model to look at a whole bunch of different examples in the training data for 100 laps of the data. So that's what the epochs variable stands for. Again, a lot of things we haven't covered here, but as I said, we're going to be writing a lot of code. And actually, I think it's about time we did that. So we've looked at some code here. We haven't written code, so we've gone against our rule. If in doubt, write the code. Let's see how we'll create some of this. And yeah, we'll create some data for regression problems. We'll write some code, and we'll get hands-on with neural network regression models. We've covered some of the fundamental principles of regression modeling with TensorFlow, specifically what is a regression problem. But now let's see how we might write some code to actually do that, or to actually work on our own regression problems. So I'm going to start a new web browser here. I'm going to come to colab.research.google.com. I'm going to create a new notebook. Now we'll wait for this to load up. Just going to zoom in here. There we go. Now I'm going to call mine O1 neural network regression with TensorFlow. And I'm going to add the little video tag here. Just as the notebook that I'm writing during the videos. If you want the ground truth notebook, so the notebook that I'm getting the information for this video off, remember you can go to the course GitHub, which is github.com/mrdbourke/TensorFlow Deep Learning. This will be linked throughout the course. At the moment, while I'm recording this, it's still a work in progress. But if you come here to O1 Neural Network Regression in TensorFlow, you'll have all of the information we're working on in a very succinct manner. So there's a lot more annotations in this one. In the notebook that we work on during the course, this one here, we're going to be focused on writing code. So if you want all the commentary around it, check out the course GitHub, specifically the notebook without the video tag at the end. So I'll just close that. And here we go. So let's write our title in Markdown. So Introduction to Regression with Neural Networks in TensorFlow. Beautiful. I'm going to turn this into Markdown by pressing Command MM on my Mac. Might be Control MM if you're using Windows machine. So we're going to write here, there are many definitions for a regression problem, but in our case, we're going to simplify it. Predicting a numerical variable based on some other combination of variables. Even shorter, predicting a number. That's what we're going to do. We're going to be writing neural network code. Did I spell anything wrong here? Probably. Definitions is wrong. Predicting a number based on some other numbers. Nice and simple. Actually, that's probably a definition for neural networks in general. But this is what we're going to start with. And we had a lecture before that was what we're going to cover. So refer to that one. But let's just get started. We need to get hands-on by, first we're going to need some data. So how about we do that? What should we start with? Import TensorFlow. So we need to import TensorFlow as TF, and then we're going to check our TensorFlow version. So for this course, we need 2 point something, so 2 plus. And you'll notice here that we're not connected to a Colab instance just yet. But the beautiful thing is, as soon as we run accel, it's going to automatically connect to a Colab instance. So we'll import TensorFlow here. Wonderful. 2.3.0. So this is the version that I'm on. If you're watching this at a later date, you might be on a later version. But as long as you're 2 point something, you should be right for this series of videos. Let's start off by creating some data to view and fit. So we had a look at what is a regression problem before, regression analysis, and it looked something like this. So we have the blue dots could be our data points, and our regression model is this red line through the middle. So that's the relationship that we're trying to learn, right? Between a dependent variable and one or more independent variables. So let's create some data that looks like this. How might we do that? Let's try NumPy as MP, and we'll also import matplotlib .pyplot as PLT. So we need to create the features, which we'll call X. Again, nomenclature for features is generally called X in the form of a capital. So this is NP array. We're going to just create this manually. Maybe we start from my favorite number, 7, or specifically -7, -4, -1. You might be able to work out the pattern of these numbers that I'm creating as well. That's what I want you to start thinking about, is that whenever you're viewing data, before you write a machine learning model or some sort of deep learning model to figure out patterns, see if you can understand them yourself. What's your gut feeling? So NP array, we'll create our labels as well, which is typically defined by Y in a lowercase. So we'll go here, 3.0, 6.0, 9.0. Now, if you were trying to figure out the relationship between X and Y, what might you do? There we go. We've got X and Y. Now, if we want to visualize it, remember one of our other mottos is visualize, visualize, visualize. We're going to see that a lot throughout the course. Boom. Plot.scatter. Okay. We've got a very simple line here. So you could think of X as our independent variables and Y as our dependent variable. If we have a look at our regression analysis little diagram, ours looks something like that, but just this has got many more samples. We're starting nice and simple. So there we go. Now, what might we want to do that? So let's try work out the pattern between X and Y just as it is. So X is -7 where Y is 3. And then X is -4 where Y is 6. And -1, 9, 2, and 12. Are you sensing a relationship here? How might we manipulate X to get Y? Well, I'll tell you the rule I just figured out. Y equals X plus 10. Does this work? X plus 10. Do we get Y? Beautiful. So if we want to go Y equals X plus 10, true, 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 true. Beautiful. So the relationship we would try to get for our neural network to learn is this here. This is the relationship or the function between our X and Y. In other words, our input features and our labels. In Wikipedia terms, our independent variable and our dependent variable. So let's have a look at what our input and output shapes. So if we were to build a model between X and Y, what might be the input and output shapes of our model? If we come back to our keynote, remember we defined our input shapes for our housing prediction problem or housing pricing prediction problem. If we were to take in these independent variables, number of bedrooms, number of bathrooms, number of garages, so bedroom, bathroom, garage, the shape would be 3, and then the output shape would be 1. And remember, these will vary depending on the problem you're working on. So in our case, our problem, if we just want to predict this simple line here, it varies from the problem we're looking at here. So if we had 3 input variables for 1 output variable here, what might be the shapes of our input and output variables for this problem? Let's create a demo tensor for our housing price prediction problem. This is a very, very important point for all the neural networks that you build. So I want you to pay attention to this one. So the house info equals, let's create a tensor. Remember our input shapes to neural networks, often numerical tensors, but this one we'll just treat it as a string tensor for now. Garage. And now the house price is going to be tf.Constant 939,700 or something like that. And now let's check out house info and house price. Okay, there's our shape. Beautiful. So what we've done is we've just converted here this demo input and output shape into actual tensors. Wonderful. So the input shape is going to be 3 and the output shape is going to be 1 because we're using the house info to predict the house price. Now in our case, we want to use X to predict Y. So, let's have a think. What might be the input shape? So if we go input shape equals, maybe it's X.shape, and the output shape equals Y.shape. Let's check the input shape and the output shape. 8 and 8. Does that make sense? Because really we want to just know what the y is based on this sample of x. And really we just want to know what the y is here based on this sample of x. So what if it was just one sample? So if we did x0, we want to use x0 to predict y0. So -7 to predict 3. And we also want to use x1 to predict y1. Just like in our housing price demo, we want to use one house to predict the price of one house, or the input features of one house to predict the price of one house. Same for this sample problem. We want to use one input feature of x to predict one y value. Same again here. So what if we check the shape of this? From this, it seems that our inputs and outputs have no shape. How could that be? I mean, it's because no matter what kind of data we pass to our model, it's going to take an input and return as output some kind of tensor. But in our case, because of our data set, it's only two small lists of numbers here. We're looking at a special kind of tensor. Do you remember when we went over the different types of tensors that you might come into? We're looking at scalars here. Specifically a rank 0, well, scalars is specifically a rank 0 tensor. So if we go x0.ndim, it has 0 dimensions. So that's why it has no shape. So let's take a look at the samples individually. So x0, y0. Wonderful. So in our case, we're trying to predict or build a model that's going to take as input -7 and produce as output 3.0. So this is where you're going to run into a whole bunch of input and output shape trouble, is when you get examples like this that don't really make sense. But how I want you to think about this is we're going to use one x value to predict one y value. So keep that in mind. And in the next video, we'll see how we might create a model to do so. In the previous video, we created some sample data, so some sample input features, and some sample labels. And what we're trying to do is model the relationship between x and y, in other words, the relationship between our features and labels. And we checked out our input and output shapes, which are kind of confusing, because when we checked out the shape of our, in our case, NumPy arrays, actually, let's turn these into tensors. How might we do that? Turn our NumPy arrays into tensors. So remember, from our TensorFlow fundamentals section, we can turn NumPy array or NumPy arrays into tensors by just passing them to TensorFlow.constant or tf.constant. And then if we wanted to check the x.shape, y.shape, well, we'll just print x and y actually. So there we go. Now our NumPy arrays are in the form of tensors. Beautiful. And we got a little confused when we checked the input and the output shape. So let's do it again while they're in tensor form. So input shape equals x0 dot shape and output shape equals y0 dot shape. Input shape, output shape. And we got a little confused because they have no dimension here, because what we're doing is when it has no dimension, it's a scalar value, so it's a single value. But then we figured out by just investigating our data that we want to use one input value to predict one output value. So that's our input and output shapes there. Now, how might we build a model to do that? How might we, not scatter, x, y. How might we build a model to figure out the relationships here? Well, we haven't covered that, so if you don't know the answer to that, that's perfectly fine. But let's start with steps in modeling with TensorFlow. That's what we're going to cover here. So, the first one is number 1, is creating a model. In here, you're going to define the input and output layers, as well as the hidden layers of a neural network. And if you're using deep learning, that is, of a deep learning model. Wonderful. Number 2, we have to compile a model. We need to define the loss function. In other words, the function which tells our model how wrong it is, and the optimizer. The optimizer tells our model how to improve the patterns it's learning, and evaluation metrics. So what we can use to interpret the performance of our model. Beautiful. And then finally, 3 is fitting a model. So this is letting the model try to find patterns between X and Y, or features and labels. Beautiful. So we have 3 steps here. Now if we come into, we've got a beautiful diagram here, which is steps in modeling with TensorFlow. Whoa, look at that. A beautiful, colorful diagram. Step 1 is we have to get our data ready. So if we were working on an image classification problem to figure out what type of food is in an image, we'd have to turn it into tensors. But in our case, we already have our data in tensors because if we have a look, we've turned X and Y into tensors. So our data is already in tensors. Wonderful. Now, step 2, once our data is in tensors, we can build or pick a pre-trained model to suit our problem. We can use pure TensorFlow or TensorFlow Hub. We'll see that in a later video. So that would be step 1 here, would be creating a model specified to your problem. Wonderful. Then we fit the model to the data and make a prediction. So that would be down here, fitting the model. But actually, in TensorFlow, building or picking a pre-trained model often involves step 1 and 2 are very synergistic with each other, meaning if you do create a model or pick a pre-trained model, once you instantiate it, you basically always have to compile it. That tells TensorFlow that, hey, I've got this model instantiated, I've got it set up, now I'm compiling it, I'm telling you that I'm ready to use it. So then we go on to step 3, is to fit the model. Wonderful, model.fit. We might fit it to the training data. We might let it look at the training data 5 times. And then we have number 4 is evaluate the model. So once the model has found patterns in the training data, we might evaluate our model on the testing data. And then if we keep going, we can improve via experimentation, and then we can save and reload our trained model. But let's go back here. Let's see how we might actually go through these 3 steps here. And what I'm going to do, I'm going to turn these into bold so they're just a little bit more pretty. Because that's what we're doing here. We're creating art. So what I might do is set the random seed so we have some reproducibility. tf.Random set seed. 42. I'm going to use 42, which is if you're wondering why I'm using 42, it's the answer to the universe. I'll let you look that one up. And then we're going to go number 1. Create a model using the sequential API. You might be wondering what that means, but we'll get into that in a second. I'm going to write the code first. Model equals tf.keras.sequential. And then we're going to open bracket. And then we have, so this is basically saying to TensorFlow, hey, I want to create a model and I want you to sequentially go through the following. We're going to just make this with 1 layer. tf.keras.layers.dense. We're going to have 1. There we go. You might be wondering why I'm using 1, because in our case, what do we want to do? We want to build a model to take as input 1 number and predict 1 number. So that's why I have 1 here. We go down. We're going to go step number 2, compile the model. So model.compile equals loss equals tf.losses.mae. So in our case, we have loss. MAE is short for mean absolute error. So let's have a look. Remember, if you don't know something, mean absolute error. What is this? So in statistics, mean absolute error is a measure of errors between paired observations expressing the same phenomenon. What about, do we have images? Comparison of two observations where x1 equals 2, mean absolute error. This is what you're going to come across. You're going to come across a whole bunch of different explanations. But what the best thing to do is to just check them out and see if something catches your eye. So examples of y versus x include comparison of predicted versus observed. Comparisons of predicted versus observed. All right. Subsequent time versus initial time, and one technique of measurement versus an alternative technique of measurement. What if we looked up just the function that we wrote, tf losses.mae? Here we go. Computes the mean absolute error between labels and predictions. Wonderful. So y true, y pred. All right. And there's the function. So it's the mean of the absolute of y minus y pred. So I'm guessing that y prediction is the prediction our model makes, and y true is the actual value it should be. So we make it the absolute value here, so it's a positive number, and then we get the average from that. Okay, so mean absolute error is just saying there's the absolute, and there's the mean. So it's just saying, on average, how wrong are our predictions? Okay. That's a little bit easier than what it first looked like. Now the optimizer is, we're going to set it as tf.optimizers.sgd. Now, SGD is short for stochastic gradient descent. Wonderful. Now, again, if you're not sure what SGD is, go, what is stochastic gradient descent? So I'll let you go through those in your own time of what stochastic gradient descent is. But just what you need to know for now is that an optimizer tells our neural network how it should improve. And then we'll go here, and we want metrics is, we're going to use MAE as well. Now, a lot of functions in TensorFlow, if they have a shortcut name, MAE or SGD, you can often use a string variable to define the fact that you want to use that specific function. So in this case, we could remove that and write SGD. But we're going to remove that. There we go. So that's our compile done. And now we're going to fit the model, which is model.fit. And we're going to fit it on X and Y for 5 laps. So this is what the fit function takes. So we create the model, we compile the model, and we fit the model, aka telling our model, look at X and Y and try and figure out the patterns. And you've got 5 opportunities of going through all of the X values and all of the Y values and trying to find those patterns or figure out the relationship. If we set this to 100, we'd say you have 100 opportunities of going through all of X and all of Y. But because we want to keep our experiments nice and short to begin with, we'll only set it to 5. All right. So before we run this, we did say that we use the sequential API. How do we find out what sequential means in TensorFlow? So if we wanted to find out what the docstring of this method here is, there we go. Colab automatically opens it up. But in my case, I'm going to press Shift Command Space as it goes here. So sequential groups a linear stack of layers into a tf.keras.model. Sequential provides training and inference features on this model. All right. So we get an example of how we can create a sequential model. Now, in TensorFlow and Keras, there's two different types or two main types of creating models. We've used a sequential API here. So we can go TensorFlow, Keras. Now this is if I already know what the difference is between the sequential and functional API is. That's a little reveal of what we're going to look into. But this is how I'd find out information about tf.Keras sequential. I go here. Sequential groups a linear stack of layers into tf.Keras model. Now there we go. tf.Keras.sequential equals layers equals none. Here's a whole bunch of different guides I could go through to figure it out. I could go through some tutorials if I wanted to. And there's actually, the documentation is showing us a different way. So we could create, this is what I also do sometimes. I just copy the code sample. I come back to my notebook. I copy it here. And then below it, I'm going to write exactly what it writes out here. So model equals tf.Keras.sequential. And then I do here model.add. Keras.layers.dense 8 input shape. Now this gives me the feeling of writing this actual code. Input shape 16. And then so on, so on. Now I want you to think about, if you've seen this example here, how might we convert our own example into this? So let's try. We'll go, we've got our sample here. We might go model equals tf.Keras, and again, looking at this one, dot sequential, wonderful. And then model.add, looking at this, we want to put this in there. Model.add tf.Keras.layers.dense 1. So there we go. We've just got reproduced the exact same thing here. Now, the reason why I'm showing you this is because in TensorFlow, there are actually a fair few ways to do things. So this is with the sequential API. You can put your layers, you can use the .add method to add them to your sequential model, or you can put them into a list, as we've done here, and add them to your layer. So tf.Keras.layers.dense.1 would be the same as adding that there. Does that make sense? If not, that's all right. Have a little bit of a play around, have a practice, check out we'll delete this cell here because we're going to use this methodology for the time being. Have a look at the TensorFlow documentation if you'd like to have a little bit more practice. Rewrite all of this code for yourself. But let's get back into here. We've set up our model here, steps in modeling. We've created a model, we've compiled the model, and it's time to fit our model. So you're ready to run your first neural network of this entire course. I hope you are. So let's try it out. 3, 2, 1. Oh, look at that. So we get a warning here. What does this say? Dense is casting an input tensor from dtype, from float 64 to the layers dtype of float 32, which is new behavior in TensorFlow 2. Okay, the layer has dtype float 32 because it defaults to float x. So we discussed this before of if you intended to run this layer in float 32, you can safely ignore this warning. If in doubt, this warning is likely only an issue if you are porting a TensorFlow 1.x model to TensorFlow 2. No, we're not doing that. To change all your layers to have dtype float 64 by default, we can set the backend to float 64. How might we just change our layer or our input data to dtype equals float? Because you see how we create it with NumPy? The default data type is float 64. So let's change the dtype to tf float 32. And same again, dtype equals tf float 32. With dtype float 32, not. Or what if we go tf.cast and then we go pass here, dtype equals float 32, and then we'll do the same here, tf.cast, dtype equals float 32. There we go. We'll change this with dtype float 32. So now we have float 32 tensors. What if we were to run this model again? Remember, this warning was telling us that the layer uses float 32 by default, but originally our input x and y were float 64. Let's run this again. Boom, wonderful. So this goes very quickly. So you can see here, this is what the output is when you're going to fit a model, is it tells us this is lap 1 of the data, lap 2 of the data, lap 3, this is how long it took, and this is our loss function, so how wrong our machine learning, our deep neural network is when we're trying to predict x and y. So right now, on average, when our model uses an x value to predict y, it is wrong by 11.5, and then it slowly improves to be wrong by 10.9. And then because we've set our metrics to be the same as the loss function, we get the same output here. So this is loss, this is our evaluation metric. Now, if we wanted to use our machine learning model to make a prediction, let's check out x and y. So right now we have a trained machine learning model. So this is tried to work out the patterns between x and y by doing 5 laps over the data. So let's remind ourselves of what x and y are. There we go. So -7, 3, -4, 6, -1, 9. Now, try and make a prediction using our model. So let's go model.predict. This is how we can make a prediction with our trained model. If we wanted to make a prediction on x equal to 17. So if we had another value on the end here, right, if we added x equals 17 to the end here, what do you think the output should be for y? If you guessed 27, you'd be correct, because that's the pattern between our x and y, is that y equals x plus 10. So let's see what our model learned. Oh, our model predicts that if we had an x value of 17, the y value should be 12.7. Now, that's pretty far off, but as we can see from our loss and MAE values, that actually reflects what our model's training output has shown us here, is that on average, our model predicts something that is basically 11 points off where it should be. So if we wanted to, let's go ypred equals model.predict, have a look at ypred. So this is on average 11 points off where it should be. Ypred plus 11, because I'm getting this value here. What does that give us? 23.7, so it's still off. So, we fit a model. Now, it doesn't find the correct patterns between x and y. So what we might look at doing in the next video is seeing how we can improving our model. So let's check out that in the next video. We finished at the last video with you writing your first neural network with TensorFlow code. Specifically, we stepped through the steps in modeling with TensorFlow. We created a model, we compiled it, and we fit the model to our data. However, our neural network didn't turn out very well. I mean, we tried to make a prediction on a new piece of X data, and the output was pretty far off where it's supposed to be. You might be thinking, hey Daniel, we kind of stepped through this code relatively quickly without discussing the concepts behind it, and you'd be 100% right with that, but there's a reason for it. If we come to our keynote, we checked out this slide, Steps of Modeling with TensorFlow. We had a brief look at our workflow, what we're sort of working on throughout this course. We had an even briefer look at the steps in creating a model, compiling a model, and fitting a model, and then, of course, evaluating it. Well, we do have a bit more of an in-depth guide as to the steps in TensorFlow modeling, more specifically talking through the code we wrote. Now, this is an important point I want to emphasize, and it's going to be a theme throughout the rest of the course, is that I would rather you learn the concepts by writing code than by looking and reading a slide. So I'll say that again. I would much rather, I held this slide back because I would much rather you write code than spend time reading slides. So if we got the steps here, Number one, construct or import a pre-trained model relevant to your problem. Compile the model. In the compilation, we define the loss, we define the optimizer, we define the metrics. Number three, we fit the model to the training data so that it can discover patterns. Epochs is how many times the model will look at the training examples. And number four is evaluate the model on the test data. Now, these steps don't necessarily come in this order all the time, but generally, you can adapt them to whatever problem you're working on. So with that being said, we've built our first neural network with TensorFlow, but it didn't perform very well. Let's have a look at how we might improve our model. So I want you to take a guess. We've got 3 steps. We're creating the model, compiling it, and fitting it. Based on what you've seen so far throughout the course, what do you think are some steps that we could do to improve our model's performance? Now, if you're not sure, that is completely fine. I just want you to have a think about it before we start going through it. Remember how we define a model? It's got a number of different hidden layers. It's got a number of different hidden neurons in each of those layers. And we fit it for 5 epochs, which means it looks at the data 5 times. So they're just a few little hints, but let's get on to here. If we wanted to improve our model, let's take a look at the 3 steps we used before to create a model. I want you to think about this, is that when we create a model using these 3 steps, we can actually improve a model by altering how we went through each of these. So when we create a model, we can improve it via steps in the creation. When we compile a model, we can improve it by steps in the compiling. And when we fit a model, we can improve the model by steps in the fit method. So let's write that down. We come here, we can improve our model by altering the steps we took to create a model. So number 1 is creating a model. If we wanted to improve our model here we might add more layers, increase the number of hidden units, also called neurons, within each of those layers, within each of the hidden layers. And we might change the activation functions of each layer. Number 2, when we're compiling a model, here we might, I've written ear up here. Here we might change the optimization function, or perhaps the learning rate. We haven't looked at this parameter yet, or hyperparameter, should I say, but we will in a second. Learning rate of said optimization function. And number 3, when we're fitting a model, here we might fit a model for more epochs. In other words, let our model look at the training data more times. So leave it training for longer, or on more data. So give the model more examples to learn from. Now, this is a very brief overview of how we might improve our model. We do have a dedicated slide for looking at this. So improving a model from our model's perspective, that is. So we might start with a smaller model, and then we might build it into a larger model. Now, before we continue with this, we've discussed the concepts of improving our model. Now, what I would rather do, instead of going through each of these one by one, is let's start to code this larger model. So we'll do that in the next video. I'll see you there. Welcome back. We finished the last video by looking at this slide here, comparing our smaller model to a larger model. Now, there's a few key differences between these two. You'll notice in step 1, here the larger model has 3 hidden layers, well, a total of 4 layers, but we've added 3 layers here to the beginning. Whereas this one only has 1 layer. This larger model has 4 layers, so we've increased the number of hidden layers. The number of hidden units, or the neurons, in each of the hidden layers is 100, whereas this one only has 1 hidden layer with 1 hidden neuron. And then if we come down here to step 2, compile the model, let's have a look. What's the main difference here? The main difference, the loss is the same, but we've changed the optimization function from SGD to Atom. So if you're not sure what the Atom optimizer is, just for now, remember, the optimizer tells our model how it can improve, and the Atom optimizer is a very common and very useful optimizer. So this will often be the default optimizer that you start with. We've also got a LR parameter here in our optimizer where this one doesn't have it. So LR is short for learning rate. In other words, when our Atom optimizer tells our model how to improve, how much should it improve each step? So the higher the learning rate, the more the Atom optimizer pushes the model to improve. Whereas the lower the learning rate, so say, for example, if we had more zeros here, the lower the learning rate, the smaller the steps our optimizer tells our neural network to take to improve. And now finally, in fit the model, we see here, we've got fit X-train subset, Y-train subset, whereas here we've got X-train full, Y-train full, and epochs equals 100 versus epochs equals 5. So what you'll often do with your data sets is split them into a subset, say for example 10% of your training data, rather than the full data set. So you can run many smaller models to make sure that they work before upgrading to a larger model. Because this larger model here may take more time to run or time to figure out patterns in the data set than our smaller model. And what do we want to do as data analysts and machine learning engineers is we want to run as many experiments as possible to figure out what doesn't work before we increase the parameters of our experiments and try run some larger models. So let's see. We're going to do it one step at a time. Let's recreate this larger model. But as I said, we'll start it. We won't change every single thing. We won't change the number of layers to begin with. We won't change the optimizer. Let's just see if we can improve it by increasing the number of epochs. So this is a very similar model to what we've built. Let's do one upgrade to it by letting it look at the training data. Rather than 5 times, let's let it look at the training data 100 times. So if we come back, so let's rebuild our model. So number 1 is create the model. Again, you could scroll up if you wanted to, but I'm just going to recreate the same model we created before, tf.Keras.sequential. And if you can't remember each of the 3 steps, so create the model, compile the model, fit the model, don't worry, because this may be the first time, or very likely is the first time you've ever written this code. However, by the end of the course, after you've built, I'm not even sure how many we're going to build, I think it's well over 100. Once you've built 100 plus models, these steps you'll start to be very familiar with. And even now, like I've built probably thousands of these, I still make mistakes and I still get things wrong and have to tweak them. So what we've done is we've created the model, which is just the exact same step we did before. It's a sequential model, meaning it's going to run from bottom to top. So you're going to pass through this one layer. We've defined our loss function as mean absolute error. We've defined our optimizer as stochastic gradient descent. And then here, we're going to define our evaluation metric as mean absolute error as well. And now, this time, in step 3, fit the model, we're going to go, this time we'll train for longer. We go model.fit x, y, epochs equals 100. So this is the exact same model as we created before up here. The only difference is here, we've changed epochs from 5 to 100. So remember, the final loss and the final MAE for this after 5 epochs was around about 11. So let's just remember 11. That's the number we're trying to get lower. That's what we're trying to improve by increasing the number of epochs. So let's try run this model. You should be very excited too. Oh, see what I mean? I've written thousands of these, but I still get it wrong. It's optimizers, not optimizer. I missed the S on the end. Run it again. Beautiful, look at that. Oh, nice and quick. How exciting is that? Epoch. So if we come down here, scrolling everywhere, right up to the top. So we see here, we've got epoch 1 out of 100. And then this is where our previous model stopped after 5 epochs. So again, the error is very similar. It's very close to 11. But then watch, as we increase the number of epochs, so 6, 7, 8, 9, 10, that's double, has the loss gone down? It has. So we're getting closer to 10 after 10 epochs. And now let's keep going down to 50 epochs. Here we go, 50, so about halfway through. Oh, we're almost at 7 loss. Okay, let's keep going all the way down. And we get to 100. Wow. Okay, so we're just below 7 here. This is amazing. So just by altering one hyperparameter of our model, specifically the number of epochs it's gone through, we've decreased our loss and our MAE, mean absolute error, from around about 11 to around about 7. So let's see what our prediction is going to be. So remind ourselves of the data. So we have X and Y. What did we try to make a prediction on before? We tried to make a prediction if we added another value here, 17, which should come out to be about 27, based on the other values of X and the other values of Y. Let's see if our model's prediction has improved. So we go here, model. If we want to make a prediction, predict, we pass it 17. The predict data has to be in the same format as the training data here, so it's in a float there. And ready? 3, 2, 1. Boom. Oh, yes, look at that. So much closer. 29.73 to what it actually should have been is 27. So much better than before. What did we get before? Let's come up here. We got 12 before. So, which is, it should have been 27. That's about 15 off. So we've reduced our error to be about 3 off. How cool is that? By just tweaking one little parameter of our smaller model and turning it closer towards being a larger model. Now, what if we were to alter another one of our model's parameters? What I'll do, before I do that, before I write the code, I'd like you to give it a try. So you see here, we've got our model code here. I'd like you to rewrite this cell. However, this time, keep the number of epochs at 100. I want you to choose one thing from this larger model slide here. It could be the optimizer to change. You could add in here one hidden layer, or you could add in all 3 to the creating a model step. But I'd like you to try one change. And then in the next video, I'm going to go through one of the changes. I'm not going to let you know which one. But just try one of these for yourself and see if it improves our model's results. Just go through the exact same steps that we've done here, creating a model, compiling the model, fitting the model, except this time, maybe add in a hidden layer here, tf.Keras ... I'll let you complete that, or change the optimizer to Atom and see what happens. So give that a try, and in the next video, I've got to decide what change I'm going to make, and we'll see if we can improve our prediction even further. Welcome back. In the last video, we saw how we could improve our model's prediction capabilities by just increasing the number of times it looked at the training data. Now, an important point to note here is that although we've seen a couple of ways of how we can improve our model, it's not always the case that any one of these parameters here, or hyperparameters, will result in an improvement. So I also issued you the challenge to see if you could change one of the hyperparameters here in creating the model or compiling the model and fitting it to the data, keeping the number of epochs the same, and seeing what happens. So depending on what you tried, it might have improved the model, might not have. But let's see if we can make another change to improve our model. So now I'm going to write some code to get even closer towards our smaller model becoming our larger model. My change, I'm going to choose by adding an extra layer here. So rather than 3 layers, I'm going to make the smallest change possible. And this is what I'd like you to think about as well going forward, is that you don't necessarily always have to add 3 hidden layers or add 10 hidden layers. You can just adjust one thing on your model, try it out, and see how it goes. In fact, that's how I would like you to run your experiments, is many, many small changes rather than always doing extremely large changes. Because otherwise, if you do too big of a change, you might not be sure what caused the improvement or non-improvement of your model. So let's go here. Let's try, I'll keep that output there. So this time, create the model, this time with an extra hidden layer with 100 hidden units. So let's go here. Model equals tf.Keras.sequential. Open a list. I like to come back right to the start here and tab in tf.Keras.layers. Now 100, and the activation on this one is going to be ReLU. We'll have a look at what that is in a later video, but if you want to test yourself at researching, have a go at just searching what is ReLU activation, or however you want to pronounce that. So tf.Keras.layers, dense 1, beautiful. Now we're going to number 2 is compile the model. Whenever you create a model in TensorFlow, you have to compile it. Compile the model, model.compile. The loss is going to be tf.Keras losses MAE, and the optimizer is going to be tf.Keras optimizers.sgd. Now I just want to show you a little tidbit just to prove that it works, is if you didn't want to write this out, you can change this to be MAE. That should work. Fingers crossed. And then metrics is going to be, metrics has to be within a list as well. Metrics is going to be MAE. Now 3 is going to be fit the model. We've got our data, model.fit, x, y. So the features come first, as you see here, model.fit. This is the doc string. X equals our features, y equals the labels. And then we're going to go epochs equals 100. So the only difference we've made to this model above is we've added this hidden layer here. So that's the one change we've made. So let's see how it goes. Shift and enter. Beautiful. Oh, would you look at that? Right from the start. Remember our first model, after 5 epochs, had an error of about 11? Well, this one's hitting about 10. But then after 10 epochs, it's already just above, it's already below our other model without a hidden layer. So this one finished off with a loss of just around about 7 and an MAE of around about 7 as well. Remember, mean absolute error is about, on average, how wrong are our model's predictions. So if we come down here, what did we finish up with here? Oh my goodness, how cool is that? Our next model, by just tweaking one little thing, by just adding an extra hidden layer here, that's all the change that we made, we've basically cut our MAE and our loss in half. So let's remind ourselves of the data. So we have X, Y. Remember, the little prediction test that we've been trying to make is if we had another X over here, which was 17, just increasing in the same way that these numbers are increasing. Let's try to make a prediction. So we want model.predict, and we want to make a prediction on number 17 to see what the Y value might have been. Oh, okay. So it should be 27. But now we're seeing it's 31.2. If we come up here, it seems that our previous model did better. It got 29.7, which is closer to the actual value it should be, 27, because y equals x plus 10. I wonder why that is, even though our loss and MAE are lower. What it might be doing is our model is overfitting, meaning it's learning the training data too well. So it's learning the patterns between x and y far too well, so when it sees a new x, it's just relating it back to what it knows. And the error that it's producing during training is not a really valid representation of what it's actually doing. See, the real way we evaluate our machine learning models is not the metrics it gives us from the training data. It's the metrics we get from data it's never seen before. Now, if we come back to our improving a model section, we saw a number of different concepts here, but let's step back through them. And I want to emphasize, as we've seen in practice, not all of them lead to an improvement of our model. And as we'll see going forward, sometimes the metrics you see here during training aren't necessarily representative of what you'll see for data the model hasn't seen before. So we're going to cover that in a little bit, but I just want to go back and step through some of the concepts that we've looked at for improving a deep model. So the first one is adding layers. We just saw that. We added one layer, and we got improved metrics during training. So when I say during training, it's when you call the fit function. However, in practice, trying to predict on a sample our model hadn't seen before, the results weren't as good as when we didn't add an extra layer. Another way to improve a model is to increase the number of hidden units. We also saw that. If we come back to our model here, we could build another one by going 50 instead of 100, and we see how this goes. So we'll train the model. That experiment ran nice and quick. Again, we're getting a fairly low loss and a fairly low mean absolute error, but the real evaluation is on a sample that the model hasn't seen before. And we get an even worse value. So we come back here. Again, this is just a great example of how improving a model, or the steps that we're looking at here, don't always result in an improvement of our model. Another way is to change the activation function, which we've tried here. So by default, if we have a look at our docstring, let's see this in practice. Activation, if we go here, get the docstring, the activation is none by default. So what if we just did that? None. And we run. What do we get here? Okay, so we get a slightly higher loss value than before and a slightly higher MAE, but again, those are just metrics during training. We want to evaluate our model on a sample that it hasn't seen. Oh, we're getting closer. 29.5. That's strange. We've reduced the number of hidden units and taken away an activation function, and we're seeing an improvement. We come here, change the optimization function. So in this example of the larger model, we're using the atom optimizer rather than SGD. So let's go back to our code. And how about we change this from SGD to atom, and we run it again. Oh, so we get a slightly higher loss than before compared to using SGD, but let's remind ourselves of the data. The training data we already have labels for. So what if we had a new sample that was 17? We want to figure out its label, make a prediction. 31, okay, so it's worse again. Change the learning rate. All right, so we have atom and it has a parameter LR. The learning rate is, if the optimizer tells our model how it should improve, the learning rate tells it by how much. So atom's learning rate, by default, Command-Shift-Enter, is 0.001. So how about we increase this? We'll increase it by 10. And for this function here, learning underscore rate can be learning underscore rate, or it can be the abbreviation LR. So let's run this again. Oh, wow. Look at that. Our loss and MAE are barely even 1. So theoretically, this model should be really good. Oh, 26.2. That's our best model so far. Because remember, predicting on 17, the ideal value should be 27. So in our case, adjusting the learning rate of our optimizer has resulted in the best change so far. So that's an important point. I want you to keep these things in your mind as we go through. And again, if you've only just experienced this for the first time, I'll give you a little hint. The learning rate is potentially the most important hyperparameter you can change on all of your neural networks. So just keep that in mind going forward. Don't worry too much about it now, but just if you want to take it one note from this slide, just write down the learning rate is the most important hyperparameter of many different neural networks. So let's go here. So fitting on more data. So in this case, we have X-train subset and X-train full. Well, in our case, we don't actually have more data than X and Y. So maybe that's our next experiment to try, is creating a larger data set. So for now, we only have 8 samples. So in practice, you'll probably have a lot more samples when you're building your neural networks. Let's come back. We've got one more, is fitting for longer. Now, this is the first one we tried, and it's actually probably one of the most easiest to try because we just adjust this from 5 to 100. So now we've seen a few different ways to improve our models and fit them to the training data. Let's have a look in the next video. We're going to have a look at a probably just as important as fitting a model to data is evaluating a model's performance. So we've seen here our test example of trying to make a prediction on a sample the model's never seen before. And we keep getting this different number. But how exactly do we tell how good our model's predictions are, or how good the patterns it's learned or the relationships that it's learned between X and Y? Let's check that out in the next video. In the previous video, we checked out a whole bunch of different ways of how we can improve our model. We even tried a few of them. Well, most of them actually. We adjusted the number of hidden layers, we changed the optimizer, we changed the learning rate, and we saw that the learning rate actually had probably the biggest influence on how our model performed. And we changed the number of times our models look at the data by altering the epochs. And in practice, this is actually a fairly common workflow. So let's write this down. In practice, a typical workflow you'll go through when building neural networks is we'll start off with build a model and then fit it, evaluate it, and then tweak a model, fit it, evaluate it, and then tweak a model, fit it, evaluate it. Yeah. And now, looking at this, you might think, well, have we actually done this? And the good news is we have. Well, that's just what we went through in the previous video. We created a model, we compiled it, and then we fit it, and then we had a look at the things that we can tweak in our models. We tried adding a layer, so we tweaked our model, we fit it, and then we evaluated it. We tried increasing the number of hidden units, then we fit it, then we evaluated it. We tried changing the activation function, the optimization function, the learning rate. We didn't try this, fitting on more data, but we're going to see that in this video, or maybe the next one. And then we tried fitting for longer by increasing the number of epochs. And because you can alter each of these, they're referred to as hyperparameters. Remember, hyperparameter is like a dial on your neural network that you can adjust to see how it improves. Whereas a parameter is usually the patterns a neural network learns. So these are the things that we don't code ourselves. So let's go back. Let's see some other ways for evaluating our model. We tried by making a prediction on an example the model hadn't seen before. But what are some other options that we have? Well, when it comes to evaluation, there are 3 words you should memorize. When we're building models, you want to experiment. But when we're evaluating models, it's visualize. So that's the most important step when we're evaluating our models. Now, what should we visualize? So it's a good idea. What I mean by visualize, we'll see in a second. Visualize, but you can probably guess. It means when we're looking at things like this, it can be hard to really understand what's going on. But when we put them in a way that we can visually see what's going on, so we might visualize the data. So ask ourselves, what data are we working with? What does it look like? We might also visualize the model itself. What does our model look like? We might visualize the training of a model. So how does a model perform while it learns? And we also might visualize the predictions. We've done this one of the model. How do the predictions of a model line up against the ground truth? The original labels. We tried this one. So this is lining up this prediction here against what it should actually be. So if we try to predict on 17, that's our x value, we know that y equals x plus 10, so it should be 27. Let's really dig into these steps here a bit further by working on a little bit of a larger problem, which is going to suit this step here, so fitting on more data. But first we'll need to make a bigger data set. And we can do that. Let's set up another x. We'll use tf range to create a range of numbers between 100, negative 100, and 100 with a step of 4. Let's see what this looks like. Beautiful. So we have 50 numbers here that start from negative 100 and increase by 4 all the way up to 96 because the maximum was 100. So 50, how many did we have in our previous x? Oh, it's not saved up here. There we go. So 8. So we got 5 times as much data. That's a good amount for now. And to do so, we're going to need to make labels for the data set. So y can just equal x plus 10. This is the formula we want our model to learn. This is a pattern we want our model to learn. Now let's have a look at y, just as before. There we go. Negative 90. Yep, negative 100 plus 10 is negative 90, all the way up to 106. So we had the same shape. So one y value for every x value. Beautiful. And now, what should we do? So it's a good idea to visualize the data. All right. So let's visualize the data. What we might do is create a plot. So import matplotlib.pyplot as PLT. Google Colab completes that for us. So plt.plot x, y. What does this look like? Oh, wonderful. How about we get that in a scatter plot? I think that's a better plot for this type of data. Yep, we should have dots there. Now, before we trained our model on x and y, and then we evaluated it on a sample our model hadn't seen before. Now, this is one of the most important concepts in machine learning and deep learning in general. And it's probably better explained using 3 sets. So before we get into visualizing the data, the model itself, the training of a model, and the predictions of a model, and even further into evaluating our model, let's take a look at the concept of the 3 sets. Now, if you're familiar with machine learning, you may already know what the 3 sets are. And so I would like you to apply your knowledge of the 3 sets. And actually, we're probably only going to use 2 sets. So split x and y into a training and a test set, only if you're familiar with it. If not, just go straight into the next video. If you are familiar with it, split x and y into an 80% training and a 20% test set. We'll see how to do that in the next video. Welcome back. In the last video, we touched upon the concept of the 3 sets. So let's dig into what I mean by that. So go here. Now, in practice, in machine learning, you're often not going to fit and evaluate on the same data set. And what I mean by that is what we did up here. We started with x and y, and we just fit the model to all of the data in one hit. And then we had to evaluate on our own custom sample. Whereas when you actually work on machine learning problems, you're often going to have 3 different sets of data. You're going to have the training set. So the model learns from this data. Now this is typically, depending on what problem you're working on, typically 70 to 80% of the total data you have available. And then we want a validation set. So the model gets tuned on this data. So this is where you would tweak different things. So if we come back up to here and we built a model, we fit it, we evaluated it, then we tweaked it. So say changing the number of hidden layers or changing the optimizer, you'll often test how these tweaks affected your model's performance on the validation set. So this is typically 10 to 15% of the data available. Again, this will generally depend on how much data you have. And then finally, you have the test set. So the model gets evaluated on this data to test what it has learned. This set is typically 10 to 15% of the total data available. So if you had a go at creating your own training and test set, you might have split it. I think I said 80 and 20%. So that's another valid training and test split. If you are going to drop one of these sets, usually you'll get rid of the validation set and you'll only have a training set and a test set. Again, will depend on how much data you have, will depend on the experiments you're running, but we've spent enough time talking about these. Let's get into coding them up. So here, if you want another analogy, you've got the slide here. We have 3 data sets, which is possibly the most important concept in machine learning, is to have the training set, which could be, if you were studying at university, your course materials, so the things you learn throughout the semester. The validation set is the practice exam, and the test set is your final exam to evaluate the knowledge you learned throughout the semester. And what we're going for here with the 3 data sets, the training, validation, and test set, is generalization. So this is the ideal state we want our machine learning model or deep learning model to be in, is the ability for a machine learning model to perform well on data it hasn't seen before. So if you've learned well the course materials throughout the university semester, you should be able to perform well on the final exam. So something you haven't seen before, if you've learned them well. Now, this is exactly what we want for our machine learning models to do, is we want them to learn patterns on the training set so that it can perform well on samples that it has never seen before. In other words, perform well on its final exam. So let's go back. Let's see how we might code these in practice. So check the length of how many samples we have. So len x, this is the data we're working with. We created this just before. By x is tf range, -100 to 100. Wonderful. Now, knowing this, we're going to skip our validation set for now. We'll see it later, but because we only have a relatively small sample, 50 is pretty small in the world of deep learning. What's a large one? Well, again, I would say minimum 100 plus samples for deep learning, but we'll see in future videos different sizes of samples. Now, the training set is typically 70 to 80% of the total data we have available. Why don't we use 80? And that means we're going to create a test set, so in other words, the final exam, of 20% of the total data available. So how might we do that? Well, we can go here, split the data into train and test sets. Xtrain, you'll often see, or this is going to be the notation for a training data set throughout the course, is just with the train tag after. This is very common in practice. Sometimes you'll see something like train data equals this. They usually just mean similar things, and the same for xtest equals or test data equals. So just going forward, if you see different variable names for training and test data, they're often the same thing. Different ways of representing the same thing. and then we'll go x test. So this will be the training data. So we want the first, because we're working with 50 samples, we want the first 40 training samples. This is 80% of the data. Wonderful. And then x test is going to be the last 10 samples. So last 10 testing samples. 20% of the data. Beautiful. And here we'll create ytrain as well, just in the same format. And we'll also create ytrain here. Oh, we've got a space there. Oh, we've got a space there too. Y40. Wonderful. And we can have a look at length of xtrain and len x test. So this should be 40 and 10 respectively. Beautiful. So what we've done is we've created a training data set and a test data set. We've also got ytrain, which are the training labels, and ytest, which are the test labels. Ytest is not defined. Ah. There we go. See? We're catching errors together. Beautiful. So we've got training features, testing features, training labels, testing labels. Now, what should we do? How about we go back to what our steps are in evaluating? So when it comes to evaluating, we should remember 3 words. Visualize, visualize, visualize. Wonderful. That's our data evaluation motto. It's a good idea to visualize the data. All right. Well, we did that before we split our data into training and test. But now let's visualize our data split into training and test samples. So how about we go here, visualizing the data. And we'll go, now we've got our data in training and test sets. Let's visualize it again. Now, if you're wondering what I'm putting here, when I write text in Colab notebooks or in Jupyter notebooks, depending on what you're using, I often write like text cells. These are just kind of notes to myself. Or if I had to share this notebook with someone else, it's information so they know what's going on, kind of like a comment, but just in a text format that's easier to understand. So that was a little bit of an aside. Let's write some code. So we want to set up a matplotlib figure, because this time we're going to be plotting 2 samples of data, our training and test. So 10.7 is my favorite plot size. So plot training data in, what's a good color? Blue. Plot scatter. We're going to go xtrain first. So we need to plot xtrain and ytrain. We can use the C parameter of plot to set as B for blue. And then we're going to label it with training data. Wonderful. And now we're going to plot test data in my favorite color, green. Plot scatter, xtest, ytest. We're going to set the color to G for green. And we'll set a label as testing data. Beautiful. And we want to show a legend so we can tell the different data apart. And we'll put this little semicolon at the end so we don't get the matplotlib output. Shift and enter. What does this look like? Ho-ho! There we go. We've got a very similar plot to just above. So this one here. Except now we have our training data in blue and our testing data in green. So anytime you can visualize your data, your model, your anything, it's a good idea. So that way it's much easier to understand. Well, in my case, I find looking at something like this much easier to understand than looking at something like this. All these numbers in a tensor. So in some cases, you won't be able to plot your data if you've got more dimensions than just X and Y. Sorry, X there, Y there. Now, what are we going to do? Referring back to our concept of 3 data sets. In our case, we haven't got a validation set. We've got a training set, which is the blue, and the test set, which is the green. So what we want to do is build a neural network to take in the training data here, to learn the relationship between X and y. And then we want to, if we want to feed in, we want our model to learn the relationship in the training data so that it can predict our test data. So if we fed it in the x values of our test data, we want our model to be able to predict the y values, so where this green line should be. So now we've visualized our data in our training and test sets, let's build a model in the next video to figure out the patterns in the training data so we can make predictions on the testing data. Welcome back. In the last video, we split our data into training and test sets. And then we had a go at, did I spell that right? Nope, again, another spelling mistake. Plenty of them throughout the course. We had a go at visualizing our data, more specifically comparing our training data to the testing data. And we want our model to learn on the training data, and we want our model to be able to predict the testing data. In other words, given x, what's the y value? So let's have a look at how to build a neural network for our data. Now, we've actually already done this. So if we scroll back up, we built a neural network very similar to what we need right up here. So let's recreate something like this. Nice and simple neural network. One layer, and we'll create it, compile it, and fit it. We'll come back down. Beautiful. So step one, I told you we're going to get lots of practice creating a model. Create a model. So model equals tf sequential. And then we'll put in one layer, tf layers, dense, one hidden unit, because remember, where our x and y vectors, or tensors, we're using one x value to predict one y value, hence why our dense layer has one hidden unit. Two, we're going to compile the model, model.compile. We need to set a loss function, tf losses.mae. And we're going to set an optimizer, which is telling our model how it should improve. Optimizers, SGD, stochastic gradient descent. And we're going to set the metrics to be MAE. Wonderful. Number three is fit the model. I'm going to do model.fit on xtrain. This time is different. We want to fit on the training data only for, let's go 100 epochs. So notice here, the important point, we're fitting on the training data, which is this blue line here. So we want our model to learn the patterns in this training data to be able to predict the patterns in the test data. So before we fit the model, I'm going to comment out this line, and I'm going to hit Shift and Enter. I'm going to instantiate our model here. Now, because what I want us to have a look at is visualizing the model. So we can get an idea of what our model looks like before we've even run it by running model.summary. Oh, what happened here? A value error. This model has not yet been built. Oh, why is that? Build the model first by calling build or calling fit with some data, or specify an input shape argument in the first layers for an automatic build. Now, you might see why I commented out this line. I did this on purpose because I wanted you to see this error. So build the model first by calling .build. So we could go model.build, and we see what that might do. So builds the model based on input shapes received. We could define the input shape there. So that's one option. That's the first one. You could try that out for yourself. Or we could specify an input shape argument in the first layers for an automatic build. So with that in mind, let's see how let's create a model which builds automatically by defining the input shape argument in the first layer. Let's see what that might look like, because this is something you'll do quite often in practice, is defining the input shape. Usually, your neural networks can determine the input shape. So this is what I mean by input shape, is this parameter here, input shape. Usually, they can figure it out, the input shape, on their own. However, sometimes you'll need to manually define it, depending on what problem you're working on. So let's see how we might do that. So we'll set the random seed. So tf random set seed for as much reproducibility as we can. So we'll create a model. This is just the same as above. And we're going to go model equals tf keras sequential. Remember, a sequential model just runs from top to bottom. We're going to go tf keras.layers dense 1. Now here's what we're going to do. The input shape argument, we need to define that. So how might we find the input shape? Remember, what are we trying to do? We're trying to predict y based on x. So what is the shape of the data that we're passing our model? X.shape. 50, but we want just one sample of x.shape. It's a scalar value. So what if we do, what is x0 and y0? What do they look like again? They're just one number. So in our case, the input shape will be 1, because we're passing it one number to predict one number. So there we go. We've specified the input shape argument. Now, again, the shape might be different depending on the input tensor you're passing in. You might have 3 different variables. So you could pass the input shape as 3. But for our case, we have one input for one output. That's what we're after. Now, we might go, number 2 is compile the model. Model.compile loss equals tf keras losses MAE optimizer equals tf keras optimizers dot SGD stochastic gradient descent metrics equals mean absolute error. So if we run this, just the same model we've created before. This is also the same as above. Now let's check out our model.summary. Whoa. Okay, we've got a few things going on here. So calling .summary on our model shows us the layers that it contains, the output shape, and the number of parameters of each layer. So the output shape here is, remember, we want one input for one output. So the output of 1, that makes sense. The layer here is a type dense. So another word for dense is fully connected. So if we go here, fully connected layer, images, what this means in a fully connected layer is that all of the neurons here connected to all of the neurons in the next layer. So that's what fully connected means. And in TensorFlow, a fully connected layer, when you see that, is the same as a dense layer. So dense is just another word for dense connections, if you see all those connections there. And then we've got parameter numbers here. Now, there's a few different things here. We've got total params, trainable params, non-trainable params. So let's define what each of these are. So the total params is total number, as you might have guessed, of parameters in the model. These are the patterns that the model is going to learn. So remember when we had a look at our overview of a neural network, it creates tensors of different values, so patterns. The total number of parameters are how many different patterns our model is going to try and learn within the relationship between, where's our X and Y data? Here, the relationship between our X and Y data. So we come down, and the trainable parameters, these are the parameters, the patterns, the model can update as it trains. So in our case, the total number of parameters here, 2, is equal to the trainable parameters. That means all the parameters in the model are trainable, so they can be updated. You might be wondering, when is ever total params different to trainable params and different to non-trainable params? Well, later on in the course, when we import a model that has already learned patterns in data, what we might do is freeze those learned patterns. So in that case, it might have a whole bunch of non-trainable parameters because we want that model that has already learned on data to keep its existing patterns. We just want to train a few parameters and apply it to our own problem. So let's write this down. Non-trainable params. So these parameters aren't updated during training. This is typical, as we discussed, when you bring in already learned patterns or parameters from other models during transfer learning. We haven't covered transfer learning yet, but we will in a future video. So this is a little bit of an overview of what you get of calling .summary. Now, if you want to have a look at what the actual parameters are in a dense layer, you're going to probably find something called a weights matrix and a bias vector. So if we go here, neural network, weights, and biases. Here we go. Fundamentals of neural networks on weights and biases. So if we look at this, basic neural network structure. So within our hidden layer, here, we've got hidden layer 1, hidden layer 2, hidden layer 3. We have a whole bunch of different parameters. Where's the weights and biases metric? There's a lot of good stuff going on here. Weights and biases. This is the type of research that you're going to have to do. Maybe that's not the best article, but Weights and Biases is a great website. Here we go, neural networks, biases and weights. We'll try another one. Or I got a better question. So here's an example of how to do better research. Is what were we actually looking for? Now I gave away there that it's a weights matrix and a bias vector. But what were we actually looking for to begin with? We don't know what the trainable params are. So if we search, what are the trainable params in a neural network? Learnable parameters. Here we go. Trainable params. Much better question. So if we come back here, this is an example of how to rephrase what you're looking for to find out in a better way. So if we come here, learnable parameters, Keras, Python deep learning, trainable params. There's a video there. Have we got here? Model.summary. There we go. Trainable params. This model has far more, 2,515. There we go. If you recall from that episode in our first convolutional layer, we haven't looked at convolutional layers yet, giving us a total of 2,515 learnable parameters. I'll leave you to do some more research here, but that's a great way to phrase a question. I have an external resource for you here while we're at it. So this is one of my favorites. We'll create the resource emoji. Resource. If you want to learn what the actual parameters are here that's going on, remember, we're focused on writing this code. If you want to learn what's going on in the background, I recommend this resource. One, you could ask a question like this to Google, or you could go to this resource for a more in-depth overview of the trainable parameters within a layer. So this will be one of the extra curriculum for this section. Check out MIT's Introduction to Deep Learning video. So we go MIT Introduction to Deep Learning. And there's a full-blown course. Here we go, Introduction to Deep Learning, intro to deeplearning.com. I'll leave this video, by the way, in the resources section. So intro to deep learning. Oh, they might be uploading it. Oh, it's a 2021. Look at that. So this is the video I'm talking about. By the time you watch this course, they may have the 2021 version. I will share the most relevant one to the course. So this is intro to deep learning if you want to learn what's going on behind the code. So the trainable params here, you can find out in that video. Otherwise, I got an exercise for you before the next video. In this course, dancing emoji. You can dance if you want, but here's your exercise. Exercise. So try playing around with the number of hidden units in the dense layer, and then see how that affects the number of parameters, total and trainable, by calling model.summary. I'll give you a demo. So if we were to change this from 1 to 3, shift and enter, and then hit model summary, look what changes, 3. So that gives me an inkling that there's 2 trainable parameters per hidden unit. That's all I'm going to let you know for now, because I want you to have a go at going through an external resource as well as adjusting the hidden units on your own and seeing what comes out. For now, all you need to do is think about these parameters as they are learnable patterns in the data we're working with. So with that being said, let's fit our model to the training data. Let's fit our model to the training data. We can do this by going model.fit. We commented this out before, actually. So just the exact same thing here. We can call that here xtrain, ytrain. Epochs equals 100. And I'm going to set a little parameter here called verbose equals 0. Remember, how can we check what that does? Verbose equals 1 by default. What does verbose do here? What does it say? Epochs verbose. 0, 1, or 2 for verbosity mode. 0 equals silent, so that means there will be no output. Progress bar, 1, that's default. Note that the progress bar is not particularly useful when logged to a file. So verbose equals 2 is recommended when not running interactively. So verbose equals 0. Oh, what happened there? We didn't even get any outputs. Because we set verbose to 0. If we set it to 1, we can watch our model train. Look at that! We'll set it back to 0. Now remember, because we're running this continually, every time we call fit, it's going to fit for an extra 100 epochs. So we've actually just fit our model for 200 total epochs. Now if we call that again, that's 300 total epochs because we've called 100 3 times. To reset that, we'd have to go up here, reinstantiate our model, get the summary. I might change this back to 1. Model.summary, and then we're going to fit it, and then we're going to leave it at that, and we'll continue on in the next video. Welcome back. We finished the last video by fitting our model to the training data for 100 epochs. We set verbose equal to 0 so we don't get any output. Now, I did also set a little exercise here. Try playing around with the number of hidden units in the dense layer and see how that affects the number of parameters, total and trainable, by calling model.summary. So let's try that out. If we call, or we'll just get a summary of our model. So model.summary. Okay, and notice this number here continually increases because we've created a total of 14 sequential models so far, at least in this Colab instance. So as I said before, when you first start writing models, you may not get familiar. By the time this number approaches 100 plus, we've created 100 plus sequential models, maybe we'll be pretty familiar with what's going on. And we had a look at the total params, trainable params, and non-trainable params, which are the patterns in our neural network, and the parameter numbers here per layer. And if you wanted to learn a little bit more about what they actually are, we've got this extracurricular resource here, so MIT's Introduction to Deep Learning video. Now, let's do a little exercise. If we were to change this to 10, we'll get model summary. Okay, number of parameters equals to 20. If we fit our model, takes almost no time at all, wonderful. We get a summary of our model. Notice here that sequential went from 14 to 15 and dense went from 19 to 20 because we instantiated a new model here. And then we've got a different output shape and a different number of parameters. So because we've got 10 hidden units in our dense layer, there seems to be 2 trainable parameters per dense hidden unit. Now, there's one more way we can visualize our model, and that's using the plot model function from Keras utility, utils, or from tensorflow.keras.utils. Let's import plot model, and then we can go plot model, and we'll check the docstring here. Is it going to come up? We'll just error it out. So sometimes when you write an import statement and the function hasn't quite been import yet, checking out the docstring by pressing Command-Shift-Enter or Control-Shift-Enter on Windows might not come up until you've actually imported that function. So that's why I just ran it. It's not going to run anything. It's going to error out because it's missing one required positional argument, but that's all right because we can check it here. Convert a Keras model to dot format and save to a file. Okay. What's the example? tf.keras.utils.plotModel model. Let's have a look at what it looks like. Model equals model. Ah, okay. So we've got an input layer. It's going to pass that to our dense layer. All right. So if we go show shapes. So if we look at what this parameter does, def plot model, model to file. If we wanted to save this as an image, we can plot it to, we can set the to file parameter. But if we want to see the shapes of our model, show shapes is by default set to false. So we want this to be true. Remember, a lot of the time we'll spend with our neural networks making sure our input and output shapes are correct. So in our case, we have a dense input layer with an input of 1 and a dense output layer with an output of 10. Although this type of model here is relatively simple, this plot model function is going to be very handy later on when we start to create more complex models with more hidden layers. So we see here, we've defined the input shape as 1. So that's why we have an input shape as 1. And our output shape is 10 because we have 10 hidden units in our dense layer. Now, how might this change if we create a tf.keras.layers.dense1, and I'm going to name it output layer, and this can be name equals input layer, and I'm going to name the whole model as name one of many models we're going to build. All right, model.summary. Now, notice how this changed. Model is one of many models we're going to build. Of course, you can name it something more specific to your problem, but you also see how we've changed the layer names. So before that was like dense 20 or something like that. We've now got a layer with the input layer name, and we've now got a layer with the output layer name. Now, this is very helpful if you have models with, say, 20 or even 5 layers. It's confusing if you're not sure which layer is which. So then we fit our model. One of many layers we're going to build. Oh, the value error. So we can't actually call our model that. So that's an invalid name. So let's just call it model 1. Model summary. Fit the model. That worked. Wonderful. Model summary again. There we go. Model 1. Layer, input layer, layer, output layer. And let's see how this updates. Plot model. Beautiful. That makes a lot more sense. So the input layer input is 1. Then we've got an input layer with a hidden size of 10. Then we've got an output layer of 1. So the input this layer takes is 10, and the output it gives is 1. Now, again, looking at this might seem quite confusing, but as I said, as we go on, as we start to build more models, as we start to visualize them, it's going to start to make more sense. So with that being said, let's stick with our theme of visualize, visualize, visualize. And in the next video, let's check out how we might visualizing our model's predictions. So, have a go at creating your own different models. Maybe add some hidden layers here, give them different names, change the number of hidden units you have here, and then fit it to the data, get a summary, see how high you can get this number of trainable parameters, and then plot the model here using the plot model utility. And I'll see you in the next video. In the last video, we saw how we could visualize the different layers in our model and also get a summary of the layers in our model, which included the number of total parameters, the trainable parameters, and the non-trainable parameters. Now, let's have a look at how we might visualize our model's predictions so we can further evaluate how our model is performing. And so, to visualize predictions, if I could type correctly, it's a good idea to plot them against the ground truth labels. So in practice, you'll often see this in the form of something like y test or y true versus y preds or y pred, whatever you want to call it, where this is the ground truth versus your model's predictions. And so to do this, we'll first have to make some predictions. So we've got a trained model. So let's look at how we'll make some predictions to create y pred. Now, it's important here that y test is usually the nomenclature you'll see for the test labels. Same with y true. And y pred is also a very common nomenclature, so a variable name, for when you're making predictions with your model, or y preds, whichever you want to do. So model.predict, and we're going to predict on the test data set. So let's have a look. Y pred, see what our model comes up with. Okay, wonderful. We get a tensor in the same format as y test. There we go. So here are the ground truth labels, and here are our model's predictions. So in an ideal world, these would be the exact same numbers. So if our model learned the data perfectly and could predict the test data set 100%, these numbers would line up with these numbers. So rather than going through them one by one and comparing, let's see how we'll visualize them. So maybe we want to, how could we do this? How about we build a plotting function to figure this out? This is in case we wanted to, we're building a function because if we wanted to visualize our predictions going forward, we're probably going to reuse this plotting function. So let's create a plotting function. And this is actually, I'll put this down as a tidbit because I want you to remember something like this. I'll put a little key here. Oh, where'd my key emoji go? That's what we want. So note, this is just a Python concept in general too. If you feel like you're going to reuse some kind of functionality in the future, it's a good idea to turn it into a function. Nice and simple concept there. So if we did want to plot it, so let's go maybe def plot predictions, and then it's going to take some training data, which will by default equal xtrain. It'll also take some training labels, which will be ytrain by default. We also want some test data, which can be xtest by default. And then what do we want? Test labels. Yes, we need that. What comes after that? Oh, of course, we'll need the predictions. So the predictions can be ypred by default. Wonderful. And we'll give ourselves a little docstring here. So what can we call it? Plots, training data, test data, and compares predictions to ground truth labels. Nice and simple. We could talk about we could put in the doc string what the different variables are, but I'll leave that up to you. And so I want to start by creating a figure. We'll set the fig size to my favorite size, 10.7. Also a great hand in poker. Plot training data in blue. So that we're just basically taking the same plotting code as above. So this is where this is coming from. I'm not just pulling this out of the air. We're just functionizing this. You could just copy this and bring it down. But since we're in the habit of writing code rather than copying pasting code, let's get some practice. So we want a scatter plot here. And we're going to do train data and train labels. So we're just taking this, train data, train labels, and we're going to put the C into blue, and we'll give it a label of training data. Wonderful. And then we'll go plot testing data in green. PLT, we want a scatter plot. Again, the plots will differ here based on what kind of data you're working with. So scatter is pretty good for the problem that we're working on here, just a nice and simple regression. So label equals testing data. Beautiful. And here's where we're going to add the extra dimension or add the extra data set. We're going to plot models predictions in red. Nice and simple color scheme. Plot, scatter, and we want to compare them to the test data. So remember, we're passing our model to make the predictions. We passed it the X, so our predictions already have the X data built in, and they're predicting the Y value. So for our scatter plot for the predictions, it's going to, on the X-axis, plot the test data, which is X test, and then on the Y-axis, we want to plot the predictions. We'll give that a nice color of red, beautiful. And the label can be predictions. And of course, we want to show the legend just in case. We know the color scheme, but in case we wanted to share this plot with someone else, show them how beautiful our model is going, that should work. So plot predictions, train data, X-train. I mean, we could look at this all we want, but hopefully Python will tell us if we've got something wrong here. Now we're going to go plot predictions. We could almost just call this as it is if all the variables are set up. Plot predictions. Boom. Oh, look at that. How good. That's some good predictions there. Now you see how this is, at least to me, I'm not sure, you can agree or disagree if you want, but to me that's something to really visualize how well our model is performing. So ideally, these red dots would line up perfectly with the green dots. But to me, that looks like something, hey, if I wanted to present this to someone else, they could pretty quickly pick up what's going on in terms of how good our model is. Now, of course, depending on the scale of this graph here, this distance here could actually be something that's way off. Now, that is where we'd want to actually compare these numbers in a different way. So I might just fill out this so we know what's going on. So train data equals X-train. We don't have to do this, but this is just for completeness. Train labels equals Y-train. Test data equals X-test. And then we go test labels equals Y-test. And then finally we finish the predictions with Y-pred. Wonderful. All right. So from the plot, we can see that our model's predictions aren't totally outlandish. However, as we said before, the distance here between these two, depending on the scale, could be a fairly large error. So the way we can figure this out is with some evaluation metrics. So let's cover that in the next video. So evaluating our model's predictions with regression evaluation metrics. So maybe before the next video, you can have a play around. Try and see if you can get that red line closer to the green line. And how you would do that is you would try to improve our model. So you go back up here, maybe add an extra layer, maybe change the optimizer, maybe fit it for longer, and see how close you can get the red line to the green line. Maybe you can get them to fully overlap. But otherwise, I'll see you in the next video. Welcome back. Last video, we saw how we could evaluate our model's performance by visualizing the predictions. Now, that's one great way to do it, but the next best way, or you can actually say these are on par depending on what kind of problem you're working on, is to evaluate our model with evaluation metrics. Now, depending on the problem you're working on, there will be different evaluation metrics to evaluate your model's performance. And so, since we're working on a regression problem, two of the main metrics you'll see. Now, again, there are plenty. You can look these up. However, two of the main ones you're going to run into are MAE, which is mean absolute error. We've been using this one so far, which is basically saying, on average, how wrong is each of my model's predictions. And then you have MSE, which is mean square error, which is very similar to mean absolute error. However, you square the average errors, and find out. Yeah, so take the errors from your model's predictions, square them, and then find the average. So that being said, let's before we implement these with TensorFlow, let's have a look at the keynote. Here we have a slide for some common regression evaluation metrics. So let's start off with the mean absolute error, MAE. Here's the formula here, written in fancy mathematical notation. Now this is just saying these are our labels here, and xi, which could also be represented by y with a little hat. We'll see that in a second. Depends on where you find this formula. I think I just found this one on Wikipedia. What this is saying is these are our labels and these are our predictions. So across all of this, when you see this, this means sum of this little fancy looking E here. I think it's a Greek symbol for sigma. Now I want to give you a little tidbit here for math. So math kind of gets a bad rap, but it's actually a beautiful way of representing nature. So when you see these symbols, and I know when I first started in deep learning and machine learning, I saw Greek symbols like this and it would freak me out. But it's basically the same thing as learning code. So it wasn't until I started to replicate these formulas in writing actual code that I really started to understand them more. And so when you see this is sum of n starting from the first sample. So across all of our samples, so take the label, minus the prediction, get the absolute value of that, meaning that if the label is, say, 10 and this is 20, so this number would be -10, but we want the absolute value. So it's going to be, remember, if we did tf.abs, which is absolute, it would be +10. And then divide it by all of the predictions that you have. So all of the samples that you're making predictions of. And when you see this in combination, so this sigma notation here with n, in combination with the divide by n sign here, we'll see another form of it in a second. This is kind of like a fancy way of writing average. And this is the absolute error. And so we can do this in TensorFlow code. We're going to see this in a second. And when to use this metric? Well, this is a great starter metric for any regression problem. It's very easy to understand because it's just basically saying, I like to think of it as, on average, how wrong are our model's predictions. So then we go to the mean square error. So again, this is a very similar way, this little setup here, of writing the exact same thing as you see here. So when you see 1 on n in combination of sigma with an n on top, this is another fancy way of saying mean. And this here is another very similar way of writing, take our labels and minus the prediction. When you see a y like this with a little hat on top, this is often standing for, remember up in our, we created ypred. So this y with a hat means ypred or y predictions, and we square it. So see here we took the absolute value. In this one, we just square it with this little 2 here, and we can write TensorFlow code to do that. And when should you use this one? Well, this is a great metric to use when larger errors are more significant than smaller errors. Why? Because of this little square here. So if you've got a model and making an error of, say, an absolute error of 10 is okay, but an absolute error of 100 is just a catastrophe, you might want to use MSE because it's going to amplify the error value for larger errors or larger values because of this little square here. And then finally, we've got Huber, which has a little bit more complicated formula. We won't dig too far into that, but again, we can write this in TensorFlow code. But Huber basically takes the combination of MSE and MAE, and it's less sensitive to outliers than MSE, so mean squared error here. So with that being said, these are some common regression evaluation metrics. Take note of this slide. You'll see these in practice. There are many more. However, let's get hands-on and start writing them with code. We'll come down here. All right. So how might we start? So if we wanted to evaluate our model using evaluation metrics, one quick way that we can do that is evaluate the model on the test set. We've got our trained model here. We can go model.evaluate, x-test, y-test. Because if we pass the test data set here, remember we want to train on the training data set, evaluate on the test or validation data set. So we come here, check the docstring, returns the loss value and metrics values for the model in the test mode. So if we run this, what's it going to give us? Comes in the order of loss and then evaluation metric. So where did this MAE come from? So if we come back up here, when we created our model, remember when we compiled it? We set metrics equals MAE. We also set loss to be MAE. So for our model, in this case, because the loss and the metrics are the same, the evaluate method is going to return the same figure. So there we go. Now, that's one quick way to start evaluating it. How about if we wanted to run one of these evaluation metrics on their own by not calling the evaluate method? We just want to compare the prediction array that we have, ypred, to ytest. Let's see how we might do that. So if we come up here, we want another cell, and let's go calculate the mean square error. Actually, let's do absolute error first because that's what we have already. Now, before I do this, I want to issue you a quick challenge. I want you to see if you can figure out, we've got this slide here. We've got the TensorFlow code for how to calculate the mean absolute error. I want you to see if you can use one of these to calculate the same value as we've got here. So you're going to have to compare ypred to ytest. So probably try type out the code here and then read its docstring and see how you might use these values to calculate the mean absolute error. So give that a go, and I'll see you in the next video, and then we'll go through it together. How'd you go? Did you manage to calculate the mean absolute error? If you had a go and you figured it out, well done. If not, let's see how we might do it. So if we come back to the slide, we've got the code here, tf.metrics mean absolute error. Maybe we'll try this one because we've already seen this in our loss function. So let's see what this is. We'll start exploring the TensorFlow library. So tf.metrics.mean absolute error. There we go. Oh, here we go. Computes the mean absolute error between labels and predictions. Beautiful, that's what we want. So that's the function that it actually implements. So loss equals mean absolute ytrue minus ypred. Beautiful. Now how might we use this? Okay, loss equals tf.keras.losses.mean absolute error ytrue minus ypred. Now metrics.mean absolute error looks like it's the same as tf.keras.losses.mean absolute error. Well, I mean, it should be because it's the same formula, right? Now, ytrue, ypred. Do we have ytrue? We don't have ytrue, but we do have ytest. So let's type that in, ytest and ypred. And actually, we might save this. So MAE equals that. And we'll set up the parameter names. Ytrue equals ytest and ypred equals ypred. See what happens. Oh, that's interesting. Now, MAE here gave us one overall metric, whereas this is showing us we've got a metric for each of our test labels and predictions. Why might that be? Well, we've actually got our predictions here and our test labels here. So what if we did ytest minus ypred? What happens there? Do we get the same output? Nope, we get a very strange output there. What if we did ypred minus ytest? We don't get the same output there. What's going on here? Let's have a look. Ypred, ytest. Now, is it because this is not a tensor maybe? Ypred? Let's turn this into a tensor and see what happens. So tf.Constant ypred. Because if we do that, have a look here, this is what happens. tf.Constant ypred. Okay, so now that's in a tensor format. Yep, that's what we want. And this is in a tensor format. Beautiful, this should work. We go here. Oh, same output as before. Let's have another look. What's the difference between these two? We'll go through it step by step. tf tensor shape equals 10, 1. dtype equals float 32. Now this is tf tensor shape equals 10, comma. That might be where I see. So they're not in the same shape. Now, this is a very important tidbit. So if we ever want to compare different tensors, remember how we did in a previous video, we had to reshape our tensors so that they could be in the same format or the right shape to do a dot product. Well, this is very similar when we're doing or running evaluation metrics. A lot of the time, TensorFlow is very smart, but it can't interpolate the fact that our ypred tensor actually has an extra dimension here compared to our ytest tensor. So, do you remember how we can remove the one dimension here of our ypred tensor? If not, that's perfectly fine. Let's revisit the squeeze method. So if we go tf.squeeze and then pass in ypred, what happens? There we go, much better. Gets rid of that one dimension there. So now our tensors ypred and ytest are of the same shape. So let's redo this. Calculate the mean absolute error. We could copy and paste that, but we're going to practice rewriting it. So calculate the mean absolute error. So let's see what happens if we go MAE equals tf metrics dot mean absolute error. Yes, that's what you want. Y true equals Y test. We're comparing, and again, this is another thing for all types of evaluation metrics. It usually involves comparing the Y true labels, so the true labels versus predictions. MAE. Oh, we forgot to TF squeeze our predictions. Shift and enter. Wonderful, look at that. How beautiful. So we get the same result as our evaluate function up here. Nice. Remember how I said a lot of the time you'll be spending your efforts reshaping tensors to make sure that they're in the right shape or the right format for whatever function you're trying to work with. Now we've done the mean absolute error. How about we try the mean squared error? So I'm going to leave this as a challenge for you. Calculate the mean square error. So just as we done before, we've got the formula here, mean square error. Try out this function here and see if you can calculate the mean square error before the next video. How'd you go? Did you manage to calculate the mean square error? If not, let's see how we might do that. We'll go back to our little keynote here. And we can see here mean square error, MSE, is very similar to mean absolute error. So tf.metrics.mean square error. Let's go back here and go MSE equals tf.metrics.mean squared error. Y true equals the test labels. And ypred equals our predictions, our model's predictions, that is. MSE. Run. what's going on here? We should have one value. You know what we didn't do? We didn't remove the single dimension from our predictions. So let's do tf.squeeze. We're going to go here and let's see what happens. There we go. Okay. Now, MSE will be typically higher than MAE because if we come back to the formula here, it's because of this little square here. So the errors are typically larger, so the resulting singular metric will be larger generally than MAE. So if we come back, when should we use it? Well, MAE is a fairly intuitive metric. It says on average how wrong are our predictions. However, when larger errors are more significant than smaller errors, so for example, if being 100 off is far worse than being only 10 off, you may want to pay more attention to the MSE. Now, you could try Huber, but I'm going to leave that to your own extension. For now, since we're going to be running some modeling experiments in some upcoming videos, it's probably a good idea to, because we also functionized our way to visualize our predictions, let's functionize. I mean, this is pretty simple, but let's make a little function for mean absolute error and mean squared error so that we can use both of them going forward. So let's, right here, make some functions to reuse MAE and MSE. Def MAE, it's going to take in some Y true labels and Y pred labels. And then it's just going to return tf metrics.mean absolute error. Y true will equal Y true and Y pred will equal Y pred. Nice and simple. And then the same thing for MSE. Y true, Y pred equals return tf.metrics.mean squared error. Y true equals Y true and Y pred equals Y pred. Beautiful. Now, do we need to do that? Not necessarily. However, it's good to have some helper functions ready to go for when we run some experiments. So let's do that in the next video. So for the past previous videos, we've made some predictions with a trained model. We've visualized them, so compared our model's predictions to the test dataset. We've also evaluated our model's predictions with regression evaluation metrics, such as mean absolute error and mean squared error. Now, the next logical step, you might be thinking, is how do we get these error values lower? So how do we minimize the difference between our model's predictions and the test labels? So in other words, get these red dots to be closer to the green dots. And so that's what we're going to tackle in the next couple of videos. More specifically, we're going to be running experiments to improve our model. Remember our workflow that we've discussed in a previous video? Usually start by building a model, fit it, evaluate it, tweak it, fit it, evaluate it, tweak it again, fit it again, and then evaluate it again, so on and so on. So if we come back to our keynote, if the Machine Learning Explorer's motto is visualize, 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 in other words, taking a look at our data, taking a look at our model, taking a look at our model's training, we haven't done that, but we will see that in a future video, taking a look at our model's predictions, and visualizing these wherever possible, well, the machine learning practitioner's motto, because we're an explorer and a practitioner, is experiment, experiment, experiment. And so that's what we're going to do. We're going to try run a series of experiments to see if we can improve our model following this workflow. We've already built a model. We've already fit it. We've already evaluated it. Now it's time to tweak it a little. We'll refit it. We'll evaluate it again, tweak it, fit it, evaluate it. So let's see what this might look like in practice. Or if we remember back, what are some ways that we can improve our model? The top three are probably you'll see get more data. So get more examples for your model to train on. In other words, more opportunities to learn patterns or relationships between features and labels. Number 2 would be make your model larger. We've seen this briefly before. So in other words, using a more complex model. That's what you'll often hear larger models referred to as, more complex. So this might come in the form of more layers or more hidden units in each layer. Remember how we added some extra layers to our models before? We also increased the number of hidden units in each of the layers. And number 3 is train for longer. So give your model more of a chance to find patterns in the data. So with these in mind, how about, since we've got our data set already, we've got X-train and Y-train. This is our data set. How might we design? We can't really do get more data unless we just artificially make our data sets bigger. So we'll rule this one out. But we can make our model larger, so use a more complex model, and we can train for longer. So let's design some experiments that we could do. How about we do 3 experiments? Let's do 3 modeling experiments. Now, what might you design? How about model number 1? What could we do for this one? So how about we do the same as the original model, 1 layer, but trained for 100 epochs. Number 2 could be model 2. This could be 2 layers trained for 100 epochs. And number 3, model 3 can be 3 layers, or maybe we won't change that. We'll keep it at 2 layers trained for 500 epochs. So 500 chances to look at the data. So see how we're just tweaking one parameter for each experiment. So the first one is 1 layer trained for 100 epochs. Then the second one, we're increasing the number of layers, but keeping the number of epochs the same. And for the third one, the difference is between the second model is the number of layers is the same. However, we're training it for longer. This is sort of the mindset I want you to start getting in. When you run your modeling experiments, start with, say, a baseline model, and then change one of the parameters for your next experiment, then do the same for the next experiment, and so on. You might want to, actually, I'll issue you a little challenge, is after you've seen us setting up these experiments, maybe you can create your own 4 and 5. So you can design them yourself. That would actually be some great practice. But let's get started. So the first one we want to do is, we'll create this. We're going to go build model 1. So what did we say? Same as the original model, 1 layer trained for 100 epochs. So we're going to set the random seed for as much reproducibility as we can get. Favorite number, 42, answer to the universe. So step 1 is create the model. So model 1 equals tf.Keros. You could scroll up and see the first model that we built, or you could just take my word for it that it was just a singular layer here. tf.Keros layers dot dense, not 1. There we go. And what's step number 2? When we're creating a model, we've created a model, what do we have to do? We have to compile it. So let's compile the model. Remember I said you're going to get a lot of practice writing this sort of code? Because that's what I want. I've said it before, and I'll say it again. I'd rather you learn concepts from writing code than from looking at slides. So the optimizer is going to be tf.Keros optimizers dot. What do we build the first model with? Oh, look at that. We get a fair few options here. Now, there's actually a fair few optimizers built into TensorFlow. The main 2 ones that I regularly use is Atom and SGD. So we can go SGD. I'll let you research the other available optimizers that TensorFlow has. we'll set the metrics to MAE. Now if we go here, fit the model, model1.fit. We're going to go X train, Y train. Now 100 epochs, that was the experiment design we were going to set up. So should this work? I think it should. Let's go. Shift and enter. Oh, look at us. Already modeling experts. So there's our first modeling experiment built. Now, what might we want to do if we're running experiments? What does a scientist do? Well, they track their results. So how might we do that? We've done it before. We created some functions before. What's the first one we might use? How about we visualize, or at least make some predictions with our model, and then we visualize them. Great idea. Make and plot predictions for model 1. So how do we make predictions with our trained model? We can we'll set up the prediction variable. We can call model1.predict. And we're going to make predictions, remember, on the test data. Because our model has never seen the test data, and we're interested in how our model performs on data it hasn't seen before. That's the real value of machine learning. Plot. We have a function, plot predictions. Oh, look at this. Look at us making our functions so we can just easily call them back again. Predictions. This is our doc string here. Plots training data, test data, and compares predictions to ground truth labels. Now, we hard-coded some of these parameters, so the only one we have to change is the predictions variable, or predictions parameter. So predictions is going to be ypreds1, because we just created that. ypreds1. Let's see what it looks like. How'd our model 1 go? Oh, not too good. So we can see there's quite a large difference here between our testing data and predictions. Remember, ideally, these would line up here, but that's all in the nature of experimenting. We're going to try and improve it. So what else could we do? Well, we also created some functions to calculate evaluation metrics. Thank you, past us, for creating such easy-to-use functions. So create model 1 evaluation metrics. So we want MAE1 for model 1, by the way, equals MAE y test, and then we're going to pass it in ypreds1. Beautiful. And then we're also going to do MSE1 equals MSE y test ypreds1. And let's see what this looks like. MAE1, MSE1. Oh no, what did we do wrong here? We forgot to squeeze these variables, tf squeeze, to get them into the same shape. Now, I guess what we could have done, if we knew that all of our prediction tensors had to be squeezed, remember, what does this do? If we visualize ypreds1, if you ever forget what something does, just create a new code cell and run it. There we go, that's what it looks like on its own. And then if we squeeze it, ypreds1, it removes that one dimension. So we have to actually turn this into a constant, a TensorFlow constant or a tensor to see that shape. So there we go. As the predictions come out, they have a 1 here, and it's our first axis dimension. But then if we squeeze it, it removes that one dimension, and it turns it into this tensor. So shape 10. So we can get rid of that now. And if we squeeze them, we can run that. Beautiful. So we see the error is quite substantially larger than what it was before. This is the MAE, so the mean absolute error. So on average, each dot is 18.74 away from where it should be. That's the mean absolute error. And if we square the errors, we see the error is even larger. Now, how about we change our MAE and MSE functions to automatically squeeze our predictions? So let's go up here. This is making our functions better. So tf squeeze. We'll go there. and tf squeeze, and we'll also go there. Shift and enter. Now if we come down here, we shouldn't need to run tf squeeze here anymore. Get rid of the extra bracket. Take note of the output here. Make sure it's the same. There we go. It is the same. Beautiful. Okay. Now that's model 1 done. So what was our second model? Model 2, 2 layers trained for 100 epochs. Now we didn't actually specify how many hidden units. I'm going to let you decide how many hidden units you should put into this second layer. So give that a try. We'll come down here. We'll go create a little note, build model 2, and then we'll just set up, so this is 2 layers trained for 100 epochs. Or better say 2 dense layers. 2 dense layers, also known as fully connected layers. Now, our first model had 1 hidden unit in its 1 layer, but I'll let you decide if we're going to add a layer to model 2. So we'll set up model 2 equals something. I'll let you decide how many hidden units there are, and I'm going to make my decision on how many hidden units there are. So give this a try before the next video, building model 2. You could even calculate the model 2 evaluation metrics and plot the results if you're game enough. But otherwise, we'll go through our second modeling experiment in the next video. Alrighty, how'd you go? Did you set up model 2? Did you run the experiments? Did it go better than model 1? Hopefully these red dots were closer to the green dots. But if not, that's all right. Let's see how we can do it. So what's our first step? We might set the random seed, tf random dot set seed for as much reproducibility as we can get. So model 2, what did we say? 2 dense layers trained for 100 epochs. All right, so number 1, create the model, tf carers sequential, and then we're going to come down here. So this one has 2 layers. We're going to go tf carers layers dense. Now, how many hidden units did you decide? If you built your own model, how many did you decide? I'm going to say 10 for this one. Remember, this is really an arbitrary number. We could set this to 1. We could set this to 10. We could set this to 100. I mean, most often you'll find values like this, like that are evened out. You'll rarely find values that are like 67, but you could try that if you want. So I'm going to try 10. tf carers layers dense and 1. There we go. And I'm also going to, what do we do? After we've created the model, what's our next step? I've given you a little hint here. Compile the model. Now we have to do model2.compile. It's going to be the exact same thing. tf carers dot losses dot mae, and then the optimizer is going to be tf carers optimizers dot sgd, just exactly the same before, and the metrics is going to be let's try MSE, you know, just to mix things up, because we're going to calculate our evaluation metrics anyway. So the only thing we've changed from our model up here is we've added an extra layer. Everything else is the same, except we're calculating the MSE as it's training. It's important to note that this metrics here will be calculated during training, and if you call, say, the evaluate method as we've done before on a trained model. So we come down, and what do we have to do once we've compiled our model? Step 3, fit the model. So model 2, we're going to fit on the same data, the training data, of course. X-train, Y-train, how many epochs are we going for? 100 epochs equals 100. You ready? Let's run our second modeling experiment. Boom. Oh, wow, the MSE starts fairly high. Remember, MSE is often much higher than mean absolute error because of the squared value. So 1084, does it decrease by the end? Surely it does. Okay, finishes on 608. Let's see, let's plot our, we've got to make some predictions. So make and plot predictions of model 2. So we'll call this one ypreds2 equals model2.predict on the test data, of course. And now we're going to plot our predictions using our beautiful plot predictions function. Woohoo! And again, all we have to change is this one. Remember, this is so helpful. If we're going to be running the same code over and over again, it's helpful to functionize it. We'll go Shift and Enter. What does this look like? Oh, yes. Very nice. So our red dots are a lot closer to the green dots. Beautiful. Come up here. Look at this one we did before. Looks like mud compared to what we've got here. So now we've plotted some predictions. Now let's calculate some evaluation metrics. So calculate model 2 evaluation metrics. You might want to pause the video and just go blaze right ahead and finish this video yourself. But if you don't want to do that, let's rock and roll here. MAE2 equals our function from before, ytest, and now ypreds2. We don't have to squeeze them this time because we've implemented that into our MAE function. And we can press Shift Command Enter. Oh, we should have actually put a doc string of what's going on here. But that's all right. We can do that later on for completeness. And then we want MSE2 equals MSE, ytest, compare it to our predictions with the second model. And MAE2, MSE2. Let's check them out. Boom, doesn't that look great? Oh, much better than before. 3.1 and 13. I think this is actually very similar to a model we've run before. But let's keep pushing on. We're now up to our third modeling experiment. So build model 3. Now, what was the experiment that we set up for model 3? We scroll back up. Lucky we took note of this. Here we go, model 3. 2 layers trained for 500 epochs. Okay, so the only thing we're going to change between model 2 and model 3, we could actually just copy and paste this if we wanted to, and then change 100 epochs to 500, so we're fitting it for longer. However, as always, we're going to favor writing the code out again ourselves. So build model 3. It is 2 layers trained for 500 epochs. Now, you could sit here and watch me write this out, or you could just skip ahead and write out the model 3 code yourself, plot the predictions, and evaluate it using evaluation metrics, and I could just see you in the next video. Otherwise, if you want to stay on board and we'll write this together, let's do it. So let's set the random seed. So tf random set seed. And then we go, what's step 1? Create a model. Oh, we are getting some prime experience here. tf.Sequential. Open up our list. We come back. What did we say? 2 layers. We're going to keep it exactly the same as model 2. So I believe it was a dense layer with 10 hidden units. Wonderful. And then another dense layer with 1 hidden unit because that's going to be the output layer. And then we're going to, what do we have to do? After we've created a model, what's our step? Compile the model. I mean, by the end of this, you're going to be like, Daniel, you are a broken record. But that's all right. If you're writing TensorFlow code like it's nothing, well, then I've done my job. Keras losses.mae, and we're going to go optimizer equals tf keras optimizers sgd. Wonderful. I'm going to set up our metrics. This time we'll revert back to MAE just to spice things up. Oh, too late. Oh, well, optimizers. Oh no, we've made a typo there. Classic. And now we're going to fit the model. So model 3 dot fit xtrain ytrain. How many epochs are we doing it for? What's our third experiment? 500. Oh, nearly did 5,000. Far out. That would have been interesting. I mean, you could do that. That's a challenge for model 4 maybe. 5,000 epochs. We'll see how this one performs first. Shift and enter. There we go. It's going to take a little bit longer, but not too much longer because it's only a small data set. But look at that. We can get ready to make and plot some predictions. Oh, what did it? Before we do that, MAE, I would have expected that to be lower maybe if we were training for longer. But again, don't just trust the training metrics. Let's visualize our model's predictions and run our evaluation functions. So let's go ypreds3 equals model3.predict. And we're going to do it on the test data set. Beautiful. And then our wonderful plot predictions function. We're going to set the predictions variable to be the predictions for our third modeling experiment. This should be preds3. Let's have a look. Oh, golly gosh. That's even worse than the first model. That's terrible. Far out. What's happened here? You know what? I think our model is trained for too long. We've totally missed the Goldilocks zone of where we should train it for. So this is a prime example of how tweaking some hyperparameters of your model, even ones that you intuitively think should result in a better result, actually don't lead to a better result. And we've actually just experienced here probably the first time we've come across our model overfitting, which is a very important concept in machine learning, but we're not going to cover it now. I'll leave that for a future video. However, if you want to look it up, I would search overfitting. Essentially, it means that the model has learned the training data too well, and it doesn't generalize very well at all to data it hasn't seen before. So give that a look in your spare time as a little extension to this video. But let's run our evaluation metrics for completeness. So calculate model 3 evaluation metrics. We'll do our MAE3. For model 3 is MAE. We'll compare the y-test labels to the y-preds for the third model. Wonderful. And then we'll do the MSE3 equals MSE y-test y-preds 3. And then we'll have a look at MAE3, and we'll also have a look at MSE3. Whoa. Now this is substantially higher than our other models that we ran. I think model 2 was actually the best one. Now, what we might do is rather than just scroll back and forth comparing our model's metrics, like we could look at that one, yep, model 2 is the best. Let's put them into a more structured manner. And so in the next video, let's look at how we might comparing the results of our experiments. So we've run a few experiments now. Let's compare the results. So in our workflow, we've said before, come back to the keynote, the machine learning practitioner's motto is experiment, experiment, experiment. But as you might have guessed, any budding practitioner or any budding scientist doesn't just experiment relentlessly. They do a few, compare them, see which one works, and then they disregard the ones that don't work and move forward with the ones that do. So let's see in the next video how we might compare the results of our experiments. Welcome back. So we've run a few experiments. Now it's time to compare the results of our experiments to see what worked and what didn't. Now again, we said we could just scroll back up and check the numbers, but that's not really a structured way. Like we've only done 3 experiments and already it's getting tedious to just go back through and see what works and what didn't. So the beautiful thing is that we've saved all of our model results to different variables. So to compare them, oh, actually, wait, I just want to put a little tidbit here. Something that I just thought of as I finished the last lecture is note. You want to start with small experiments and make sure they work. So by small experiments, I mean small models, and then increase their scale when necessary. Because what's our motto as a machine learning practitioner? Experiment, experiment, experiment. And it's hard to run a lot of experiments when you're trying really large experiments all the time. So start small, like we've done up here with our first model, model 1. We started with 1 layer, and then we started to increase the complexity as our experiments went on. So just keep that in mind when you're running experiments. Start small, build up, add complexity when needed. So let's go down here. And if that doesn't make sense for now. We're going to see that a lot throughout the course. It's going to be our theme, is start small, build up when needed. Let's see how we can compare our results. So how might we do so? Well, how about we create a pandas data frame, which is just a table so we can compare our results of a different model. Let's compare our model's results using a pandas data frame. So the beautiful thing about Colab is that it's got pandas inbuilt. Import pandas as PD. And then we'll probably set up our model results as a list of lists. So we can pass it to our... So model 1 can be MAE1, MSE1, and then model 2 can be MAE2, MSE2, and then model 3 can be MAE3, MSE3. Beautiful. And then to create the data frame, how about we call it all results? And then we'll go PD data frame. And then the first thing we'll pass it to is our list of lists, so model results. And then we can set up the column names. What should we call the columns? Well, we have models, MAE, MSE. That's nice and easy. So model, MAE, MSE. Beautiful. And now what does this look like? Is it going to work? It worked, but that's a little hard to read. You know what we can do here? We can just get the NumPy value of all of these. So we go .NumPy. Maybe we could have built this into our functions up above, but because we're already here, we'll just do some hacky code to get it looking nice. But when you're writing your code, you're going to make it beautifully functionized, aren't you? Let's see this. There we go. That looks much better. So, from our experiments and comparing our results in this beautiful table, I mean, maybe if you run a few more models down here, you may have model 4, model 5, model 6, etc., etc. It looks like model 2 performed the best. So what was our model 2? Model 2.summary. So it looks like it had 2 layers. So one with 10 hidden neurons and the output layer with 1 hidden neuron. And it was fit for, we can come back up here. We can see it up here, model 2, 100 epochs. All right. So, what can we do with this? You might be thinking, comparing models is very tedious. And it definitely can be because we've only compared 3 models here. But this is part of what machine learning modeling is all about. Trying many different combinations of models and seeing which performs best, and actually seeing which doesn't perform best. So each model we ran is an experiment to figure out what doesn't work. And I'm going to put a tidbit here, is that we'll just write here, looks like model 2 performed the best. Wonderful. So the tidbit, the takeaway here is, this is a follow-on from before. So we said start with a small model, and another one is one of your main goals should be to minimize the time between your experiments. So that's why we start small and build up when needed, because, as we said before, if you're having to wait like 10 minutes between each model experiment, and sometimes you will have to with a larger data set, as we'll see in future videos, but the more experiments you do, the more things you'll figure out. Now this is getting too big because it's not a markdown cell. The more things you'll figure out which don't work. And in turn, when you know what doesn't work, you will get closer to figuring out what does work. It takes a lot of trial and error. Remember, the machine learning practitioner's motto: experiment, experiment, experiment. By the end of this course, you're going to have that tattooed on your brain, as well as, if in doubt, run the code, and as well as visualize, visualize, visualize. And so another thing here is that what you think might work, such as with Model 3, we increase the number of epochs, so the number of times Model 3 could look at the data. Sometimes intuitively you'll think it will work. We mentioned this in the previous video, but it in fact turns out to be the exact opposite. So look what happened with Model 3. So that's why experiment, experiment, experiment is so valuable. Now you're probably wondering, it's like, Daniel, hey, we saved all of our results here and we kind of set up a pandas data frame and we had to save all of our evaluation metrics to different variables. I mean, you say here, we're probably going to run potentially dozens of modeling experiments per problem that we're working on. That's going to end up very tedious and a lot of different stuff all over the place. And you're exactly right. Well, the good thing is that the people, like machine learning practitioners around the world, have developed solutions. And so I'm going to put here, tracking your experiments. These are a couple of little extensions for now, but we are going to cover one of them in the future. So let's just put here, one really good habit in machine learning modeling, as you may have seen, is to track the results of your experiments. And when doing so, it can be tedious if you're running lots of experiments. Luckily, there are tools to help us. So the first one, this is a resource. We're going to put the little resource emoji here. Resource, remember, all of the resources, exercises, extensions, etc. in the course GitHub, as well as going to be links there'll be links where you can find all of these things. So resource, as you build more models, you'll want to look into using. So one of my favorite tools built straight into TensorFlow is TensorBoard. So this is a component of the TensorFlow library. And again, I'm just introducing the names of these things now, but later on we're going to get hands-on. So TensorBoard is a component of the TensorBoard library to help track modeling experiments, a very important part of machine learning, and we'll see this one later. And another one of my favorite ones that links straight into TensorBoard, there's a fair few of these on the market, but this is the one I have the most experience with. It's called Weights and Biases. So a tool for tracking all kinds of machine learning experiments. And the beautiful thing is, plugs straight into TensorBoard. So if you're using TensorBoard, you can definitely use Weights and Biases. So if we have a look, we can search up TensorBoard, tensorflow.org/TensorBoard. Here we go, TensorFlow's visualization toolkit. We're not going to dive too deep into this. If you want to jump ahead and have a look at what TensorBoard is capable of and maybe even plug it into our models, you can check it out. Otherwise, the other one is Weights and Biases. One of my favorite external tools for machine learning. But since this is outside TensorFlow, we're not going to be covering Weights and Biases. You can look into that as some extra curriculum if you want. We will be seeing TensorBoard later on. But for now, that's all we're going to cover for tracking our experiments. In the next video, if we've trained a model, say Model 2, and we wanted to use it, say, in one of our applications, what we might want to do is get it out of our Colab notebook and somewhere else. So let's look in the next video at saving our models. So we've trained a few models and we found out that from our modeling experiments, Model 2 is performing the best so far. So let's say we wanted to save that model. Like right now, it's just sitting in our Jupyter Colab notebook. It exists as a Python object here. How would we save that and export it somewhere else? So let's figure out how we might do that. I'll just put a note here. Saving our models allows us to use them outside of Google Colab or wherever they were trained, such as in a web application or a mobile app. So how might we save a model in TensorFlow? This is where I'd start if I wasn't sure. I'd look it up. There we go. Save and load models. All right. Caution, TensorFlow models are code and it is important to be careful with untrusted code. See, using TensorFlow securely for details. I'll let you have a look at that, but trust me, we're not using TensorFlow maliciously here. Now, we've got a few options here. So defining a model. They've created a function here to define a model, model.summary. Here we go. We could save checkpoints during training if we were training for a long time. We're probably actually going to have a look at that later on in the course. But where is the save model function? What if we go save? There we go. Model.save. Save the entire model as a saved model. Now, in TensorFlow, there are two formats, or two major formats of which you can save a model to. The first one is the saved model format. So the saved model format is another way to serialize models. Models saved in this format can be restored using tf.Models.load model. Okay, so that's, I'm guessing, once we've saved our model. If it's in saved model format, we can load it in using this method here. And are compatible with TensorFlow serving. We haven't seen that, but if you wanted to look it up, that's something you could look that up. The saved model guide goes into detail about how to serve/inspect the saved model. All right, well, we've read up a little bit about it. Let's try it. Oh, and what's down here? Another format. Okay, so it looks like there's two formats that we can save our models in, but they're both using the save method. And one has a .h5 extension, HDF5 standard. All right, well, let's try one at a time. So how might we save a model? Or we'll put a note here. There are two main formats we can save our models to. Number one, the saved model format. And number two, the HDF5 format. Now, I believe the saved model format is the default. Actually, I know it is because I have experience with this, but let's just see. So save a model using the saved model format. Now, we can do so, go model2.save. And then if we check out the doc string here, saves the model to TensorFlow saved model or single HDF5 format. Okay. The save file includes the model architecture, allowing to reinstantiate the model weights, in other words, the patterns our models learned, the state of the optimizer, allowing you to resume training exactly where you left off. That's handy. All right, so let's try it out. So what was the parameter we have to pass in first? File path. Or let's call it something simple. You might want to get more creative with your model naming. So I'm just going to call mine best model saved model format and shift and enter. What happens here? We get a whole bunch of warnings. So I've looked at these warnings before, and they come up a lot of the time when you're saving a model. Essentially, what it is some behind-the-scenes libraries that have been updated, and if you're just using the save format, you can safely ignore these. You can also find what the warnings actually are in this documentation here. But just for now, trust me, the save model format, if these warnings come up, it's all right. Unless you're getting some sort of failed, the model hasn't saved correctly. But in our case, let's have a look at what happens. We check the Files tab of Google Colab, and here we go. We get best model saved model format. And in this file, we get a few things. We get assets. Okay. So we got what's in here and what's in the variables. And we get saved model.pb. Now this .pb format is called a protobuf file. Again, you can find more on this in the save and load documentation. But to make sure that our model's saved correctly, one of the best ways that we can do it is by loading it back in and checking it out. But before we do that, how about we save a model in the HDF5 format as well to test that out. So let's search that. HDF5 provides a basic save format using the HDF5 standard. All right, what's the HDF5 standard? Hierarchical data format. All right, is a set of file formats, HDF4, HDF5, designed to store and organize large amounts of data. Okay, well, I'll let you know that going forward, you're probably going to start training some fairly large models. And sometimes you might need to store them in a universal data format. So something like hdf5, so something that you can pass around to many other different programming applications. And TensorFlow allows us to save our models directly to .h5 by adding the h5 extension onto the end of our file path. So let's have a look at that. We're just going to run the exact same code up here, except one difference. Save model using the hdf5 format. Now, which one of these should you use? Well, it's really going to depend on your use case. If you're staying within the TensorFlow environment, so you want to just use your model with pure TensorFlow code, you're probably better off using the saved model format. However, if you're going to use your model outside of pure TensorFlow code, maybe hdf5 is better off for you. But we're getting a little bit ahead of ourselves here. Just know that there are two main formats that you can save your saved models to. The save model one is also the default, so the majority of use cases you'll probably be using the saved model format. Now let's see what happens if we run this. See how we've just got the exact same code here, but all we've done is we've changed it to have .h5 on the end. We'll run that. Beautiful. Now what happens? There we go. So you'll notice the main difference here as well is saving a model to the saved model format. We get a folder here. And to the .h5 format, we get a single file. Now, I mentioned before that a way that we can check to see if our models have saved correctly is by loading them in and testing them out again. So much like we've evaluated our model 2, I'll just close this to get these evaluation metrics here. If we load our model back in, if the documentation is correct, saying that it's saved all of its weights and optimizes state, when we load our model 2 back in from its saved model format or the h5 format, theoretically it should get the same results as before we saved it. So in the next video, let's see how we can both load a model in and reevaluate it to make sure it's saved correctly. Welcome back. In the last video, we saw how we could save our models, or a trained model. And we saved them both to, or model 2, which is the best performing model so far, to both the saved model format and the hdf5 format. So we've still got our models here in the Files tab of Google Colab. Now, what if we wanted to load that model back in? Let's see how we do that. Loading in a saved model. So if we come back to the documentation where we looked at load and save models, there we go. So new model equals tf.Variable models.load model. Now I believe if we go load model, there we go. Models saved in this format can be restored using the tf.Variable models.load model method. Now the beautiful thing is that with both formats in TensorFlow, the save model format and the hdf5 format, we can use the same method to load them in. So let's see how we do that. Which one do we want to do first? Load in the saved model format model. Let's do, what could we go on? Loaded saved model format equals tf.Variable.models.load model. And then we're going to pass it the file path of this folder here. Now in Colab, you can do this by copying the path. So I'll just show you that there. We can copy the path there, turn that into a string. Now, again, in Colab, you're going to get a little content in the front of it. I believe it works regardless of whether you have content in the front or there or not. So we could do it like that. Hopefully that works. Otherwise, we can just revert back to what we want. Load save model format. How should we evaluate it? Oh, we'll get a summary. That's how we do it. Summary. Let's see if this works. Beautiful. Now, is this the same as our model 2 above? We've got 2 layers, dense, with 10 hidden units, and another one here with 1 hidden unit. If we go model 2 dot summary, is that the same thing? Yes, beautiful. Now, to see if our loaded saved model format model, far out, we're going to say model a lot here, aren't we, is actually still the same as model 2, because right now the architectures we've confirmed are the same. And these are the same here. However, in the documentation, it told us that it's going to save the weights as well. So in other words, the patterns model 2 has learned. So to really check that, how about we make some predictions with model 2 and the saved model loaded model, and then compare those predictions to make sure they're making the same predictions. Because if they are, that means the patterns they've learned should still be the same. So compare model 2 predictions with saved model format model predictions. So this is kind of like we're writing a test to see if our models are the same thing. Our loaded model and our saved model. And we're going to go loaded saved model format preds equals loaded saved model format dot predict on X test. And then to compare them, we could do, let's just test them for equality. How about we do that? Loaded saved model format. This should return true. False, 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 false. What's happened here? Let's have a look at model 2 preds. And loaded saved model format preds. 528 13991. They seem pretty comparable to me. What we might have to do is, how about we calculate the mean absolute error of each? Otherwise, we might have to bring in a NumPy function here. So MAE, we want MAE of y true equals y test, and y pred equals, this is going to be model 2 preds. And then we want to compare these two to MAE y true equals y test, and y pred equals loaded saved model format preds. So they should have around about the same error. How does this go? True. Beautiful. So I'm not sure why their predictions are different. You know why it might be? It's because of how a computer stores numbers. So if we go model 2 preds, have a look at this. Maybe we'll squeeze that so it's, by the way, you can do dot squeeze on the end if you wanted to. That's a NumPy method coming in there, I believe. Yeah, there we go. And then if we do loaded save model preds dot squeeze, I believe these two should be very similar, yeah. So why aren't that? If we copy this up here, we're going against our rule of always writing code. Should this equal true? True, 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 true. Okay, so I would say the reason why here we're not getting this correct is because dimensionality-wise, they aren't of the same shape. Is that why? But that doesn't make sense. So this is I want you to experience this. This is me exploring an output that I didn't really expect while I was creating this video. So I really want these videos to be as if like we were sitting side by side and coding and figuring things out together. That doesn't work. Okay. Oh, you know why? Because it's not preds. Haha. What a simple typo. Did you catch that? Why didn't you tell me earlier? Haha. This is a challenge we face when we're bringing in so many similar variable names. Now this should work. Okay, true, 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 true. All right, all that extra code there we wrote, well, the news is we didn't have to write it. So, I mean, you're going to see these things happen a lot of the time. And I'm glad you're watching me make mistakes on the fly, because as you learn, you're probably going to make a lot of mistakes too. Now, we've loaded in a model using the save model format. How about we try the H5 format? So load in a model using the .h5 format, and we're going to go loaded H5 model can be tf models.load model. And then we're going to pass it in just the file path. We can come over here, copy the path if we wanted to, Command V or Control V, depending on if you're on Windows. I'm going to turn that into a string, get rid of that. Now again, you don't necessarily need content, but just to check if it works. So that's the loaded model, and we'll get the loaded H5 model.summary just to make sure it's the same thing. Does this match our model 2 summary? I believe it does. Model2.summary. So first things first, that's nice and easy to check. The architectures are the same. Now we're going to check it to make sure its predictions are the same as model 2. So if we go here, check to see if loaded.h5 model predictions match model 2. So we can go model 2 preds. We've already got that variable, but we'll just have some practice writing predict on x tests, writing some more code. It never hurts to write a little bit more code. And then we'll go loaded h5 model preds equals loaded h5 model dot predict on x test. And then if we want to compare them, we can remind ourselves to this time add preds on the end, Daniel, equal loaded h5 model preds. How do we look here? True. Beautiful. We could do the same again for working out the MAE, but I'm just going to, if all the predictions are the same, the MAE should be the same as well. So we can get rid of this extra one and maybe move this one up to the loaded save model format. We'll just put a note in here of what we did so we don't confuse ourselves when we come back to our notebook. Compare the MAE of model 2 preds and loaded saved model preds. So what we just did, we repeated ourselves writing the code here. If you wanted to sort of functionize this going forward, that could be one of the tests that you run. So say, for example, you saved a model and then you loaded it back in. You could write a little function to make sure that the loaded model has the same prediction values or error rate or summary or something like that as your saved model. That way you make sure you're using the same the model with the same learned patterns. But otherwise, in the next video, we have our files here in Colab. How might we download them to our local machine if we wanted to use them outside of Colab? Let's check that out. Welcome back. So we've seen how we can both save a trained model and load it in within a Google Colab notebook. And by the way, a lot of these methods will work in just a Jupyter notebook. But how might we download a model or any other file from Google Colab? Now, this will be this lecture specifically if you're using Google Colab. If you're using a Jupyter notebook, oftentimes your files will be on your local machine or on your server hosted somewhere else. But this is specifically if you wanted to get a file off Google Colab. Now, we've got a couple of ways. So the first one, number one, or if you want to download your files from Google Colab, number one is you can go to the Files tab and right-click on the file you're after and click Download. So let's try that out. So Files tab, this is this one here. We have code snippets, we have search, we have table of contents. Far out, look how much we've covered so far. You should be really proud of yourself. But we'll come into the Files tab because that's what we're trying to do. And say we wanted to download our best model HDF5 format, .h5, we could just go here and click Download. Now, depending on the size of the file, will depend how long this takes. But now if we check My Files, Downloads, I've got the best model HDF5 format saved here in my download. So if I wanted to import that into some sort of application or into another coding environment, I've got it saved and trained here. Now, the second option to download a file from Google Colab is we can use code. see the cell below. Let's write some code to download from Google Colab. If we want to download a file from Google Colab, we can import from google.colab, import files, and then files allows us to files.download, and then if we just pass, we'll copy this one, see if we can download it again, copy path. We pass in the file path of our .h5 model, shift and enter. Oh, has no attribute downloaded. Oh, type that in wrong, so don't type in downloaded like I did, just type in download. And here we go. We're going to get a little loading bar, and there we go. We've got another copy of it. So we'll check the downloads. Oh, there we go. We've got the same file because I've got a little 1 here because we downloaded it twice. But that is a quick and easy way if you wanted to download your files from Google Colab. Remember, depending on the size of the file and your internet connection, it may take a little while to download. So just be patient. The other way is, maybe a third way is if you wanted to, while we're here, you can save it to Google Drive by connecting Google Drive and copying it there. So see second code cell below. So let's see how we might do that. I'm going to mount my Google Drive. So this is going to, if you have a Google account, which you kind of require to sign into Google Colab, it's going to mount your Google Drive, which is online cloud storage hosted by Google. We're going to wait for this to load. And when it loads, we should see our drive file appear in the Files tab. Beautiful. So this is my Google Drive here. If I open that up, I've got my drive, and I've got a few other things that I'm working on there. Wonderful. So if I wanted to save it here, copy path, or actually copy path there. Let's save a file from Google Colab to Google Drive. This requires mounting Google Drive. So we can do bang cp for copy. So we're going to copy this file here, h5. So that stands for copy this file at this path to, which path do we want to go to? I believe I might have a TensorFlow course. I'm going to copy that path. Now you might have to create a file in your Google Drive called TensorFlow course. You might be able to go new folder and create something like that. But mine's called TensorFlow course. It's already existed. So there we go. Copy best model hdf5 format.h5 to content drive my drive TensorFlow course. Let's see if this works out. All right, that looks like it went through pretty quickly because it was a relatively small file. So let's go ls and then just the path here to see if it's copied across. Oh, best model hdf5 format.h5 and a little spoiler alert for what's to come, but I'm not going to talk about that for now. We're going to see that in upcoming videos. So there's 3 ways there. If you wanted to download a model or any other file from Google Colab, you can right-click and click download. You can download it with code. Or if you wanted to save it to your Google Drive and access it later, you can use the copy method to save it across there in your target folder. Alrighty, so we've been through a fair few of the fundamentals. In the next video, or in the next series of videos actually, let's have a look at how we might tackle a larger example. And I'm not going to say any more. I'm going to wait until you're in the next video to show you what's going to happen. I'll see you there. I've said it before, and I'll say it again. We've covered a lot of ground so far. I mean, we've seen the fundamentals of building neural network regression models in TensorFlow, so you should be proud of yourself. Look at all the subheadings we've covered. Give yourself a pat on the back. But now it's time to step it up a notch and build a model for a more feature-rich data set. So have a look at our data. Look at what we've been playing with. X-train and Y-train. Just a couple of tensors with single numbers trying to predict single numbers. But In practice, you're probably going to be dealing with a little bit more of a complex data set. So, what data set are we looking at? Well, we're going to have a look at the publicly available medical cost data set, available from Kaggle and hosted on GitHub. So, let's find it. So, medical cost data set. Here we go, medical cost personal data sets from Kaggle. Now, Kaggle is a website which is basically an incredibly great place to compete in data science competitions, find different data sets, see example notebooks, and also learn more about data science and machine learning in general. So you're going to become very familiar with Kaggle over your data science and machine learning explorations. So we're not going to go through it for now, but just know that if you want example data sets, Kaggle is probably one of the best places to find them. Now, if we have a look at this, so medical cost personal data sets, insurance forecast by using linear regression. Let's have a read of what's going on. So context, so machine learning with R. So R is another programming language that can be used for numerical computing, just like Python, by Brett Lantz. Is a book that provides an introduction to machine learning using R. Okay, so the long story short here is that this is a data set that's available online, and we've got a bunch of columns here: age, sex, BMI, children, smoker, region, charges. Now what we're trying to do here is use these columns, so age through to region, to predict what someone's individual medical costs billed by health insurance will be. So we're using these features here to predict a number. So it's a regression problem. I believe this example has used linear regression, but we're going to build a neural network regression model. So the dataset is publicly available on GitHub here. Wonderful. So there's a fair few datasets here. We're looking specifically at insurance.csv. Now I'll show you a little trick that we can use to import this straight from GitHub to our Google Colab notebook. If we go raw, there we go, raw.github user content. Now, if you can't find this link, I'll put in the resources section for you. We're going to copy this link, come back to our notebook. I'm going to get out of this. And the first thing we're going to do is actually import the required libraries for this larger example. We've already imported these, but it's good practice just to, if we were starting from scratch, import TensorFlow as TF, import pandas as PD. Wonderful. And we're going to also need matplotlib in case we want to do some plotting. Those libraries are pretty standard. So now, because we've got the insurance data set copied to our clipboard, read in the insurance data set. Let's see what it looks like. We'll call it insurance equals pd.readcsv. And then the beautiful thing is we can just paste a link in here, and the readcsv function will read it directly from here. All of these values. So there's the columns: age, sex, BMI, children, smoker, region, charges. We can import directly. Let's have a look. Insurance. All right, so 1,338 rows times 7 columns. Yes, now we're talking. This is a little bit more complex than the problem we've been working on so far. So what do we have here? We have age, sex, BMI, children, smoker, region, and then charges. This is an amount. So this is how much someone's medical costs or medical bills were, medical insurance was based on their age, sex, BMI, number of children, are they a smoker, yes or no, and whereabouts do they live? Southwest, northwest, etc. I'm not sure. Is it from a city? Anyway, doesn't matter. You can do some research. I'll put the links to where you can find this data set. Essentially what we're focused on here is writing TensorFlow code to take in these features, learn the relationships between them, or more so the relationships between these features and this target variable here, charges. So what is a regression problem? Relating it back to our Wikipedia definition, in statistical modeling, regression analysis is a set of statistical processes for estimating the relationships between a dependent variable, often called the outcome variable, and one or more independent variables, often called predictors, covariates, or features. So in our case, what is our dependent variable? Our dependent variable is the charges, because this is what we're trying to predict. And what are our independent variables? In other words, known as, I like the term features. So that's what you'll hear me use a lot. Our independent variables are these columns here: age, sex, BMI, children, smoker, region. So what do we have to do? What is our first step in getting our data ready to pass into our machine or neural network models? Could we just start building a model? Model equals tf keras sequential. I mean, we could keep that going, but what do our machine learning models like? Can we pass in this column, sex? If it reads female or male, what's it going to do? So if I go insurance, what type is this column? Oh no, insurance. Data type object. Well, what about smoker? Data type object. What's the difference between smoker and insurance age? int64. So we have some columns here that are numerical and some columns that aren't numerical. Do you remember what we have to do to non-numerical columns before we can pass them to a deep neural network or a machine learning model? We have to turn them into numbers, right? If we come back to our regression inputs and outputs, say we're trying to predict the price of homes, the sale price of homes, based on the features here, bedrooms, bathrooms, garages, before we can pass it to our machine learning algorithms, we have to create a numerical encoding, which is often referred to as input features. So that's what we're going to have to do to these variables here. Now, one style, we've covered one style of numerical encoding, and it's the style we're going to use for this problem. It's called one-hot encoding. So if we go, what is one-hot encoding? Probably one of the simplest methods to turn categorical variables into numerical variables. So if we go here, is there a diagram? Maybe we just go to images. There we go. Nice and simple. So one-hot encoding, if we have the food name apple, chicken, broccoli, for one-hot encoding, apple gets a 1 and 0 for everything else. For chicken, chicken gets a 1 and 0 for broccoli and apple. For broccoli, broccoli gets a 1 and a 0 for chicken and apple. So that's what we want to do. Because we're working with categorical variables here, we're going to create a column that is maybe sex underscore female. And if the value of this sample is female, we want to put a 1 there. And if it's male, we want to put a 0 for the sex underscore female column. Now, we could do this manually, but that's going to take a whole bunch of work. So what I prefer to do is use, if we go to pandas data frame, we can use pandas get dummies function. Let's see what this is. Or better yet, if you didn't know what this function was called, how to one-hot encode a pandas data frame. What do we get? How can I one-hot encode in Python? One-hot encoding a feature on a pandas data frame. Examples. What do we get from this web page? Again, I'm not sure what this web page is going to show us, so this is kind of running the gauntlet here. All right, there we go. With one-hot encoding, a categorical feature becomes an array whose size is the number of possible choices for that features. So we create a data frame of country, different countries here. Wonderful. They use get dummies. Pandas provides a very useful get dummies. So once we'd seen that, gives a great example there. Beautiful. We could go to the get dummies page, but we already have that open. Get dummies. Convert categorical variable into dummy/indicator variables, which is I'm not sure why they use dummy indicator variables. I just treat this as another name for one-hot encoding. Come down. We see some examples with pandas. There we go. All right. So let's just run some code and see what happens. Rather than diving into documentation, who needs the docs when you can just run hundreds of different little mini experiments and figure things out for yourself? No, that's not to say that documentation is actually very valuable. So get used to reading documentation but also get used to writing lots of code. So let's see what happens if we run this. Data frame object has no... Oh, we can't run it like that. Oh, I'm eating my own words here. We have to run it like this. pd.getDummies, then pass it our data frame. Come on, Daniel. pd.getDummies. Let's try one hot encode our data frame. So it's all numbers. And what do we call our data frame? Insurance. Oh, yes, look at that. Okay, that's what we want. So we have age, BMI, children, charges, and now for the columns that were categorical columns, such as sex, we have sex, female. So see here, this first sample has a value of female. So it gets a 1 for the sex underscore female column. And then for the sex underscore male column, gets a 0. And then were they a smoker? Yes, they were a smoker. Oh, maybe why? That's why their charges are so high. So they get a 1 for the smoker yes column. And where were they from? They were from the Southwest. So they should have a 1 in the Southwest region. Wonderful. Okay, that looks good. Now, we might actually save this to a variable. Insurance underscore 1 hot. And then insurance 1 hot. Dot head. Excellent. All right. So now we have a few more feature columns. So because charges is still the column we want to predict. So we want to use all of these columns, age, BMI, children, sex female, sex male, sex no, smoker no, smoker yes, region northeast, etc. We want to combine all of those and learn the relationship between what charges equals. So we'll probably end this video here before it gets too long. But if you want to have a here's a bit of a challenge too. If you want to go ahead, maybe we'll, in the next video, create X and Y values. So features and labels. Have a go at creating the X and Y values. Then we'll need to create a training and test set. And then we can build a neural network. So here's your challenge. If you want to go ahead, create training and test sets, and then build a neural network. It'll be sort of like Model 2 above, but it might have different input and output shapes, or we'll see. But that's your challenge if you want to go ahead. Otherwise, in the next video, we'll start to tackle these 3 things. How'd you go? Did you take on the challenge? Did you create X and Y values, features and labels? Did you make a training and test set? And did you perhaps even build a neural network, sort of like Model 2 above, to find the relationship between our features and target variable? If not, that's perfectly fine. If you did, wow, that's incredible work. Otherwise, either way, we're going to go through each of these 3 steps in this video. So let's split these off. I think the command is command M minus. Yeah, there we go. If you want to split a cell, so command or control M minus in Google Colab. So we have 3 different things here. This is what we have to do. All right, create X and Y values, features and labels. Let's do this. X equals. Now, what did we say before are our features? Basically, every column except charges. So let's, how can we do that? We can drop a column. So insurance 1 hot dot drop, and we're going to drop charges on the first axis. I believe that's how we do it. If not, we can find out in a second. And then Y is going to be just this column. So let's make sure we can get that. Insurance 1 hot, just charges. Wonderful. Okay, now let's view X. X dot head, first 5 rows. Wonderful, age, BMI, children, etc., etc. Got a fair few columns there, and let's view Y to make sure. Remember, always visualize, visualize, visualize. Beautiful. There's the charges there, which are all float 64s. Now, these are in a format of, right now, they're in a format of a pandas data frame. However, we're going to see very shortly that we can turn them into formats capable to be used with our neural networks. That's actually probably going to happen automatically because we're about to create training and test sets. Now, previously, we'd indexed our data sets going something like the first 40 examples are training examples. However, there's a much better function to create a training and test set if you've got a feature matrix and a label vector. So we're going to use scikit-learn train test split. This is a very popular function. Model selection, train test split. Remember, creating a training and test set, probably one of the most important things in machine learning. That's why this function is so beautiful. So split arrays or matrices into random train and test subsets. Wonderful, that's exactly what we want. Oh no, we don't need to copy that. We can just import sklearn.model selection train test split. Let's see how we can use this. From sklearn.model selection import train test split. So if there's one function from scikit-learn you want to remember, it's this one. Very, very popular. So we go here, xtrain, because it's so useful. xtest, ytrain, ytest equals train test split. And then we want to, can we get the doc string? Or is it not imported yet? Not imported yet, that's all right. I know you need an input, but we're not up to that yet. Here we go. What's the doc string? Split arrays of matrices into random train and test subsets. Okay. So we want, what does it take? Arrays, sequence of indexable with same length or shape 0. Allowed inputs are list, NumPy arrays, SciPy sparse, matrices, or pandas data frames. That's us. That's what we have. Beautiful. Test size. If float should be between 0.1 and 1.0 and represent the proportion of the dataset to include in the test split. So before we made an example, right up the top, right back up here, in the 3 sets, we used an 80-20 split, meaning 80% training data, 20% testing data. That's a very common split, very useful split for our problem. So let's keep it at that. And I just want to see, what's the example here? This is where I got this line of code, by the way. Okay, train test split, it passes x, y, test size equals, they've used a 33% test split, and they've set random state 42 to make sure that the data is split in the same way each time. So otherwise, if you don't set the random state, the split will be random. So let's go in here. I'm going to pass x, y. Oh, I've got caps lock on. Goodness gracious me. Test size equals 0.2. And I'm going to set the random state. They've set 42, so we'll set 42 too. All right. And let's see what happens here. We'll go len x, just to see the length of x overall, and then length of x train and length of x test. What's going to happen here? Beautiful. Look at that. It's created our train and test split. So this is how many were originally in x. And because we've set the test size to 0.2, our test data set has 20% of the sample. So if we were to go 0.2 times 1338, what does it give us? Okay, it's going to be around, it's been rounded up. All right, nice and fair. And it's also random. So if we go x train, what does that look like? Ah, all right, all these indexes are randomly shuffled. Beautiful. That's what we're after. So let's get out of that. Now, how might we build a neural network to take in x train and y train and learn the relationships between the two? So the hint is, it's sort of like Model 2 above. So if we go, we get another code cell here, model2.summary. What does Model 2 look like? All right, so we've got 2 layers. Very familiar with this Model 2. How about we just recreate it? What should we do? TF, set the random seed first. Random set seed 42. Nice. Now step 1 is create a model. How do we do that? We go model, or actually we'll call it insurance model. There we go. TF. Pretend we're working for a large insurance company and we've been asked to model this data set so that when Sally Smith comes to buy insurance off us, we know if she tells us how old she is, where she's from, if she's a smoker or not, we know how much we should charge her based on our other customers. That's what we're doing now. There we go. Now, what do we do always after we create a model? Step 2 is we compile it. Compile the model. And here it's called insurance model.compile. What's our loss function going to be? tf.losses. What have we been using? MAE, mean absolute error. We can keep it like that. We could even change it to MSE if we were feeling a little adventurous. But since we're going to stay with a similar experience to what we've been running, we'll keep it as MAE. Optimizer equals tf optimizer dot the old faithful stochastic gradient descent, SGD. And the metrics we're going to put here is mean absolute error. Beautiful. And now, number 3 is we fit the model. Now, I said before we were going to format our data into a way that it's going to work with TensorFlow. So right now we're writing TensorFlow code here, but up here, this is Pandas code. Pandas, scikit-learn, and now TensorFlow. I wonder if this will work. Do you reckon it'll work? If in doubt, run the code. You ready? We're about to build a neural network model on 1,000, or really because we're fitting on the training data, it's just over 1,000 rows of data, which is a big increase on what we've been working with so far. So, don't hold your breath. 3, 2, 1. Is it going to work? What did we mess up? I knew there'd be an error. Spelt insurance wrong. Oh, what an anticlimax. All right, 3, 2, 1. And again. Here we go. Here we go. Now all the typos come out. All right, third time lucky. 3, 2, 1. I'm done. Oh, you typed in. All right, no countdowns anymore. Just fit the model. Boom, look at that. All right, now this one takes a slightly little bit longer because we're working with more rows. So we come down here. Does our MAE decrease as we're going up? It starts off around 8,600 and it finishes around 7,100. Okay, so a fairly good decrease. And we're just going to get rid of this cell here. Wonderful. So what do we do now? We just train a model. Oh, and yeah, by the way, we didn't even have to reformat this into tensors. The reason being is because Pandas is built on top of NumPy. So really, when we see it like a Pandas data frame, this is actually a big NumPy array. And when we pass that to TensorFlow, it automatically knows how to deal with NumPy arrays because we've seen tensors work with NumPy arrays before. So what's next? After we've trained a model, what should we do? Should we evaluate it on the test data? Great idea. Let's do that. So check the results of the insurance model on the test data. So insurance, how can we do that? We can use the evaluate method, evaluate on X test, Y test. Let's see how it performs. All right, okay. So on the test data set, it's performing even just a slightly little bit better than on the training data set. That's pretty cool. So now what might we want to do? What is this error telling us actually? Mean absolute error. It means that on average, our model is wrong by about 7,000. Now, is that number large? Is that significant compared to the other values in our data set? Let's have a look at our training variables. Y train. Whoa. So if our model is off by 7,000, what's the median, the middle number of our target variables? Wow. So the median variable, or actually what's the mean as well? 13,300, 9,500. So right now our model's pretty substantially wrong because, I mean, look at this. The average value of Y-Train, so the average insurance cost, is 13,300. So, and our model is on average off by 7,000. That's pretty significant considering the total amount is only 13,300, well, that's the mean. But the median, it's even worse. It's only 9,500. So if we're off by 7,000 there, we might be charging someone 2,000 when they should be being charged 9,500. So naturally, what might we want to do? If you guessed improve our model, you'd be 100% correct. So let's, in the next video, right now, it looks like our model isn't performing too well. Let's try and improve it. So we're going to start to run some experiments to improve our model. But before I do, again, I'm going to issue you another challenge. If you want to go right ahead, we've already run some experiments to improve our models. How about you try running some very similar experiments on the model we just built here? Maybe you add an extra layer, maybe you change the optimizer, maybe you train for longer. Give it a play around and see how you go. But otherwise, we'll try a few experiments in the next couple of videos. How'd your modeling improvement go? Did you get a better MAE score? Was it lower? I hope yours did better than the one we first built, but if not, that's all right. We're going to see if we can improve it now. So what should we do first? When we did it up here, we did some experiments. So the first thing we did was, okay, we added an extra layer. Okay, let's try that. We'll come down here, a larger example. First experiment. Might write this down actually. So to improve our model, or actually we'll put try. To try improve our model, we'll run, let's do 2 experiments. So one can be add an extra layer with more hidden units. And then 2 can be train for longer. And then I'll leave the rest up to your imagination. Insert your own experiment here. You can put to use what we've learned. So how about we recreate the model? We'll try the first one. So add an extra layer with more hidden units. So set random seed and then tf random set seed. Wonderful. Now, number 1, create the model. So tf carers, oh, we need to go insurance, what do we call it before? Just insurance model, right? Insurance model 2 equals tf carers sequential. Wonderful. And then we should go tf carers layers. Maybe the first one here has 100 now. Then tf carers layers dense 10. And then tf carers layers dense 1. Is that an increase? What was our first? Yeah, we only had 1 layer with 10 there. So this model has an extra layer with an extra 100 hidden units. So if we come down here, if we go there, 2 is compile the model. And we want to go insurance model 2 dot compile. We're going to go loss equals tf carers losses dot mae. What's the optimizer? tf carers optimizers. One day I'll get this right. SGD, beautiful. And then the metrics can be MAE as well. And now let's go number 3 is fit the model. Is insurance model 2 dot fit x train y train epochs equals 100. All right, you ready? This time we're going to set verbose equal to 2, so we don't have a massive output. Verbose, sorry, equal to 0. What do we get wrong here again? Oh, metrics equals MAE. All right, we finished there. Again, we get some warnings. It's just saying that our data types are maybe not optimized, but the beautiful thing is that TensorFlow fixes those for us. And now we can go evaluate the larger model. So insurance model 2.evaluate. Hopefully, because we've added more hidden units and an extra layer, we've given our model more potential to learn. So, well, that's at least in theory. Did it work? Oh, what do we get wrong here? Maybe we should output the training. Nan. Hence 100, insurance model 2, insurance model. All right, now we definitely have some troubleshooting to do. What have we got? X train, Y train should be the same. Maybe our model is too complex to learn anything. So we might have built a too big a model. What's another lever that we can tune here? We could remove this layer. Let's see if we just remove that layer. Does this work? Okay, so it works there. This is some good troubleshooting. Now what if we keep that layer on and try again? We get loss is NaN. If you ever see your loss or MAE as NaN, it means that there's probably something wrong with your model. So this is some good troubleshooting. Now, let's think about this. We've got to create the model. Our first experiment, we put down here that we wanted to add an extra layer with more hidden units. Yes, but it looks like our model may be too complex for our data set, so that it's not even, it's so large that our data set is not large enough to teach it anything. So what we might try to change is, we haven't looked at anything in number 2. Now, can we alter the learning rate? So the learning rate is 0.01. How about we try Old Faithful Adam? So there's a few different optimizers here. SGD and Adam are probably the most popular. If SGD doesn't work, try Adam. Let's see what happens. Ho ho ho! Look at that! Yes! Oh! That's so far so good. That looks like it's doing better than the previous model. All right, evaluate the larger model. Ho ho, look at that. Now, we've just, if we go insurance model, where's the first one? .evaluate, X test, Y test. What were the metrics from this one? MAE, holy goodness. We've just decreased it by 2,000. So about 30-odd%, around about. 30-odd% decrease in error rate by tweaking 2 little things. We added an extra layer and we changed the optimizers. Again, this might not always work, but that's just one of the levers that you can turn on your models to improve them, or at least try to improve them. We put that up here on purpose to try improve our model. So I'm going to put here, we actually modified this experiment, add an extra layer and use the Adam optimizer. So this one we're going to train for longer, same as above, but train for longer. Maybe 200 epochs. 500 probably too many. Well, who knows? If in doubt, run the code. Experiment. Okay. So that's insurance model 2. Let's run insurance model 3, see if we can improve on this number here. How do we create this? So set random seed. So tf random set seed 42. Beautiful. Now, number 1 is create the model. Same as above. So we'll go insurance model 3 equals tf.Keras sequential. Go right to the end here. tf.Keras layers. The first layer we had there was a dense layer with 100 hidden units. And now we have tf.Keras.layers dense 10. And then tf.Keras layers dense 1. Got to make this insurance company happy, you know. What's step number 2? Compile the model. Beautiful. Insurance model 3 dot compile. Loss equals tf.Keras losses dot MAE. That deleted itself out of nowhere. The optimizer is, remember what optimizer are we using now? We're using Adam. Optimizers. Come on, Daniel, you can remember that. And then the metric is MAE. Wonderful. And now let's have a look. Number 3 is fit the model. Insurance model 3.fit xtrain ytrain epochs equals 200. We might actually put this history equals that. You'll see what this means in a second. So you ready? Let's run this. 3, 2, 1. All right. We're past 100 epochs. Oh yes, the MAE is going down. Beautiful. Woohoo! All right, so if we go, now let's evaluate. Evaluate our third model. .evaluate. Do these results on the training data set translate to the test data set? Because that's what we're really concerned about. Evaluate. That is what's up. We've decreased our MAE to 3,500. I believe we are now, so if we look at back to our first insurance model evaluate x test y test, we just halved our error rate in about 5 minutes. How cool is that? Now there's a few more levers that we could try, but there's also a little thing that I want to show you. And we saved history equals insurance model 3.fit. What is this history variable? Well, this is something we're also going to get very familiar as we go. So plot history, also known as a loss curve or a training curve or a training curve. So how we can do this, if we go pd.dataframe equals history. So history has a history parameter saved to it, or attribute, sorry. And then if we go dot plot, inside a pandas data frame that is, and then we're going to set the y label to loss, and then the x label to epochs. And shift and enter. Look at that. One of the most beautiful sights you will ever see in machine learning and deep learning is a loss curve decreasing. So, why is this so beautiful? It's because if we look at where this history variable originates from, we instantiated it when we started to fit our model to the training data set, specifically insurance model 3. Now, if we scroll right back to the top of the epoch chain here, all the way up to 0 out of 200, look at this. The loss starts at a massive 13,273. So the MAE, when our model first started to learn, its average prediction was off by 13,273, which is basically the average of the whole data set. But then we scroll down, as our model trains, as it learns, its loss goes down, its MAE goes down, and we finish off with a loss of 3,600, and because our loss function is MAE, we finish with an MAE of 3,600 as well. And this is what this curve is reflecting. So when we're training our neural networks, generally we want our loss curve to go down, because that means that the predictions our model is making are becoming less and less wrong. So it actually looks like our model's loss would probably keep decreasing, maybe not as extensively as it has here if we kept it training for longer. So that's probably a little extension that I'll leave for you to try out for yourself. Train the insurance model 3 for a few more epochs, maybe another 100 or 200 or so, and see how low the loss will go. But you're probably asking, after seeing this, how long should you train for? Well, that's a great question. Let's put that there, actually. We'll do the question emoji. Question. How long should you train for? So if you're asking that, I'm going to hit you with an answer that's going to say, it depends. Remember how machine learning and deep learning is very experimental? Well, how long should you train for is, it actually really depends. Really. It depends on the problem you're working on. However, many people have asked this question before. So, TensorFlow has a solution. It's called the early stopping callback. And we're going to use this in a later video, but I just want to introduce it now so it seems familiar. So, TensorFlow early stopping callback. Here we go. And essentially what this is this, I'm going to set the link here, early stopping callback. I'll let you read what the documentation says, but I'll just tell you. It's called the early stopping callback, which is a TensorFlow component you can add to your model to stop training once it stops improving a certain metric. So, in the case of our insurance model 3, if we wanted to say train it for 1,000 epochs, we could set the early stopping callback to say, hey, I'm going to set you off train for an unlimited amount of epochs. But once your loss stops decreasing for say 3, 5, or 10 epochs in a row, which means our model has stopped improving, stop training. All right, does that make sense? Now, a little extension you could do would be to look at the early stopping callback in TensorFlow and see how you could implement it for the code that we've written here. All right, but otherwise, I think this video is getting a little bit too long. So we've covered a few modeling experiments here. What we're going to look at next is another way of pre-processing data, specifically normalization and standardization. So again, if you want 2 pieces of extra curriculum before the next video, read up on the early stopping callback and search for what is normalization and standardization, and think about how it might relate to our training data. But anyway, I'll see you in the next video. Welcome back. So in the previous few videos, we've been putting together all of the different concepts that we've learned so far, and there've been a fair few. We started working on a larger example, specifically trying to predict the cost of someone's medical insurance based on features such as their sex, BMI, where they lived, and smoking status. Now, we've got one more thing we're going to cover before we move on to the next section. And it involves pre-processing data, specifically to do with normalization and standardization. Now, you may have heard of these terms before. If not, that's perfectly fine. We're going to go through them. You might be thinking, hey, Daniel, why are we going back to pre-processing data? I thought we already had our data ready. We'd turned it into tensors, we'd one-hot encoded it, etc. And you'd be 100% correct, but there is one step we can do to improve the pre-processing of our data. So if we come back to our keynote here, this is our steps in modeling. And you might have noticed, if you hadn't looked at this in a while, we've actually done each of these steps throughout this entire section. We've gotten our data ready, we've turned it into tensors, we've built a TensorFlow model, we fit the model to the data and we've made predictions on the data, we've evaluated our model through both visualization and using evaluation metrics, we've improved our model through experimentation, and we've saved and reloaded our trained model. But now we're going back to step number 1, possibly the most important step in this entire pipeline, getting our data ready, turning it into tensors. So we've turned all our data into numbers. Remember, neural networks and actually most machine learning models can't handle strings. They need everything to be in numerical form. Number 2, we've made sure all of our tensors are the right shape because, as we've seen before, if our tensors are the wrong shape, we run into a whole bunch of different issues. And number 3, we could do, or we haven't done yet, is to scale features. So normalize or standardize. Now, neural networks tend to prefer normalization. Again, these are just words to you at the moment, but we're going to see what both of these are in a minute. So let's go back to our notebook. Again, if you wanted to figure out what normalization and standardization are, what could you do? Here's what I would do. Let's go, what is normalization in machine learning? If we zoom in here, so we got here, normalization is a technique often applied as part of data preparation for machine learning. The goal of normalization is to change the values of numeric columns in the dataset to a common scale. Without distorting differences in the range of values. All right, so let's have a look at our dataset. Xtrain, or maybe just X as a whole. What does X look like again? So, we see here we've got age, BMI, children, but do you see here how age is on a different scale to what BMI is? So if we go X, what do we want? We want age dot plot. So see how these values are all over the place? That's probably not the best plot. Maybe we can go hist. We want a hist. Oh, we need the kind word. There we go. Okay, so here's the distribution of our age column. Now, what about our BMI column? We want plot kind equals hist. It's like this. So what if we wanted to get these both on a similar scale? So see, this goes from 20 to 60, this goes from 15 to 50, and then children, I'm assuming goes from something, if we go X children dot value counts, what's the max number of children? Value counts. So there's a lot of people with 0 children, and there's a few people with 5 children. So what if we wanted to get these, so 15 to 50, 0 to 5, and 20 to 60, what if we wanted to get all of them, say, between 0 and 1? Well, that's what normalization does. If we come back up here, the goal of normalization is to change the values of numeric columns in the dataset to a common scale. Okay, beautiful. Now let's come back to the keynote. Feature scaling. So we have some options here. Now, the scaling type of scale, a lot of different names are used for this, but I'm going to be referring to it as normalization. But if you hear scale features, typically they're referring to normalization. And what it does, converts all values to between 0 and 1 whilst preserving the original distribution. The distribution of our data is just the spread. So here we can see that the most values occur. What's this? This is BMI at about 30. And as we get towards the tails here, the values start to spread out. Whereas the distribution of age is pretty fair along all the values. Maybe most people in our sample are about 20 years old. So we come back here. Now, if we wanted to do this, we can do it with scikit-learn using the min-max scaler. And when should we use it? This is often used as the default scaler with neural networks, and it's the one we're going to get hands-on with. Another very common scaling type is standardization. What it does is it removes the mean and divides each value by the standard deviation. You can use the standard scaler scikit-learn function. And when to use this one? Maybe you want to transform a feature column to have a close to normal distribution. But remember, if we scale our features or standardize our features, this reduces the effects of outliers. So if we come back, this is a normal distribution. Let's have a look. Normal distribution. What does a normal distribution look like? All right, there, also known as a Gaussian. So we come here. If we were to change this age column to be a normal distribution, what would happen? It would reduce the effects of this outlier value here. So see how this column, if we reduce them all to be the shape of that, the tails we might lose out there. Now, what are we going to focus on? We're going to focus on normalization. So if we go here, in terms of scaling values, neural networks tend to prefer normalization. Now, how might we do this? Well, actually, let me just put a little tidbit here. If you're not sure on which to use, you could try both and see which performs better. Now, one more resource I want to show you before we actually get hands-on in code is Jeff Hale's article on scale, standardize, or normalize with scikit-learn. So this is a phenomenal article. I'll make sure it's in the resources section for you. But if you want to read through this for a bit more information on what scaling is, what the different kinds are, why you should do it. So here we go. Here's a great reason. Many machine learning algorithms perform better or converge faster when features are on a relatively similar scale and or close to normally distributed. Examples of such algorithm families include neural networks, which is what we're building. But we're going to see this. I don't want you, again, to just continually just learn from reading things. I want you to write code to see it for yourself. So let's jump into that. Enough talking, Daniel. All right, what's this first step? What should we do? We might import, we'll start again. We'll start fresh. So import pandas as PD, because I want you to be able to just come to this section in the notebook later on and just run it straight from here. Then we want to import matplotlib.lib.pyplot as PLT, and then import TensorFlow as TF. Wonderful. And then we'll read in the insurance data frame. So we go here, insurance equals pd.readcsv. We'll have to come back up and copy the URL, just the same URL we used as before. There we go. We're going to copy this one just to reinstantiate this data frame. That's all we're doing, so that we can start from scratch and see what pre-processing our data or normalizing our data does. Here we go. We'll make sure it's a string, and then we'll check insurance. Beautiful. All right. So we've discussed the concept of pre-processing data, normalization and standardization. We come back to the keynote. We've discussed the names of them, but now it's time we're going to get hands-on. We've reinstantiated our insurance data frame. In the next video, we're going to go through normalize the numerical features, and we'll also prepare the non-numerical features as well, and then we'll fit our neural network. So I'll see you there. Welcome back. In the last video, we discussed the concept of pre-processing data in terms of normalization and standardization. Now we're going to get hands-on normalizing the numerical features of our insurance data frame here, and then we're going to build a neural network to learn on the features once they've been normalized. So let's see this in practice. Alrighty, how can we do this? So to do this, we're actually going to borrow a few classes from scikit-learn. So what I'll do is I'll code it up and talk through it as we go. You follow along as best we can, and then we'll discuss it once we've gone through it. So first of all, we're going to need, or actually, to prepare our data, we can borrow a few classes from scikit-learn. Wonderful. Okay, so from sklearn.compose, we're going to need make column transformer. Remember, you know how to look up the docstring of these things now, so you can see what these mean if you're not sure, but you could probably guess. Import, we're also going to need min-max scaler, and I'm not pulling this name out of the air, one-hot encoder. If we come back to our keynote, scale or normalization, we can use the min-max scaler in scikit-learn. So we come back. Now what we're going to do is create a column transformer. This is very helpful. So why do you think it might be called column transformer? Well, if you've guessed, because we have columns here and we need to transform them in some way before passing them to our neural network, you'd be correct. But let's see it in action. Let's call it just CT for column transformer. We'll run make column transformer, and we might just run this cell first so that we can see what the docstring is for make column transformer. Here we go. Construct a column transformer from the given transformers. And we come here, transformer estimator, columns, string. Where's an example? Example, here we go. So make column transformer, standard scaler. Oh, where have we seen that one before? That's this, standard scaler. And what else was there? One hot encoder. All right, so we're actually going to need both of those, but instead of standard scaler, we're going to use min-max scaler, which is transform features by scaling each feature to a given range. So the default is between 0 and 1, which is what we want with normalization. So let's see this in action. We're going to pass it the columns or the column names that we need to normalize. So let's put a note here. Turn all values in these columns between 0 and 1. Now, how did we know this? It's because when we look at our data, when we explore our data, we've got age here, we've got BMI, and we've got children. These are the numerical columns. We don't need to scale this, our target variable, but we might want to scale our feature variables. And we know for the sex, smoker, and region columns, we're going to one-hot encode them just as we've done before. So let's come down here. And now we need to make a one-hot encoder. And we're going to set this parameter to the handle unknown equals ignore. So this just means if there's any columns that the one-hot encoder doesn't know about, just ignore them. And then we're going to pass it the columns we want to one-hot encode. Smoker and region. Wonderful. So have all the brackets correct? Yes, there we go. Beautiful. Now we've got our column transformer ready. So as we pass our data through this, it's going to get min-max scaled on these columns and one-hot encoded on these columns. So now let's create our X and Y values because remember we just re-imported our data frame as a fresh. So X is going to be insurance.drop charges. And then we'll do that on the first axis. Y will be, what are we trying to predict? We're trying to predict charges. Beautiful. No typos there. And now, what do we want to do next? We've got our X and Y, but what do we want our model to learn on? Remember our 3 data sets? We want to train our model on some training data and evaluate it on some data it hasn't seen, in other words, test data. So the beautiful thing here is that we can use scikit-learns. Oh, we should put this up here from sklearn dot model selection import train test split. So now let's build our train and test sets. So we want xtrain, xtest, ytrain, ytest equals train test split x, y. Test size equals 20% of a test data set. And the random state we're going to set to 42 so that the split happens exactly the same as you can scroll up before as we did before. Otherwise, it'll be random and we'll get different results. So now we're going to fit the column transformer to our training data. So the important thing here is that whenever you have some sort of column transformer, you want to fit it to your training data and then use that fit column transformer to transform your test data. Because otherwise, if you do that separately, remember the test data is data the model has never seen before. So it's basically data from the future. So if we're transforming our training data set with information from the test data set, it's like taking knowledge from the future and altering the data that we have now. So let's go here, ct.fit on xtrain. Now we want to transform training and test data with normalization, min-max scaler, and one-hot encoder. So let's go xtrain normal for normalized equals ct.transform. So now we're taking what we've learned from the training data and we're transforming it. We're normalizing the features and one-hot encoding the features that we've defined up here. And now we've got xtest normal equals ct transform xtest. Beautiful. So now we've been through a fair few steps here, but when we break it down, we've just created a column transformer with the minimax scaler and the one-hot encoder. We've turned our data into features and labels. We've split our data into training and test sets. We've fit the column transformer to the training data only, and then we've transformed our training and test data with normalization and one-hot encoding. Let's see what, oh, we got a typo here. Beautiful, that runs without errors. Now, we've normalized our data and one-hot encoded it. Let's check out what it looks like. What does our data look like now? So we want to go xtrain.lock. Let's look at the first one. Oh, sorry, we want to go, oh, well, that's what it originally was. So then if we go xtrain normal.lock. Oh no, maybe we just want the first one. Alrighty. So here's what we started with. Age is 19, sex is female, BMI 27.9, children, smoker, region. Now we've got a value here. I'm guessing that's the age. This must be the BMI. This must be the children. And now all of these other values are 1 or 0. Beautiful. So is that the same for another sample? And how about another sample? Wonderful. Well, what does the whole thing look like? Ah, it's all in numerical format. Now what does that mean? Well, if you guessed, we can pass this to our neural network as all encoded data. You'd be 100% correct. So let's check the shapes. One more thing. Oh, we'll keep that sample there. And then we'll check the shapes of our data now. How has our shapes changed? So xtrain shape and xtrain normal.shape. Ah, okay. So you see our xtrain value had 1, 2, 3, 4, 5, 6 different columns here. Well now, since we've normalized it as well as one and hot encoded it, we've actually added some extra columns here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Alrighty, so it looks like that our data is ready to build and pass to a neural network model. So what we might do is, actually, I'll write a text cell. We'll write beautiful, because it is beautiful. Beautiful. Our data has been normalized and one-hot encoded. Now let's build a neural network model on it and see how it goes. So the challenge for you is to now build a neural network model to fit on our normalized data. So you probably want to build one similar to the insurance model we built before. Just in the same way we've been doing it, build the model, compile the model, fit the model, and then evaluate it. So fit the model on the training data set, and then evaluate it on the test data set. So if you want to give that a try, go right ahead. But otherwise, we'll take care of that in the next video. Welcome back. Did you give it a shot? Did you try building a neural network to fit on our normalized data? If not, that's perfectly fine. That's what we're going to do in this video. So let's get started. We'll set the random seed so we can have as much reproducibility as possible. Let's set seed, 42. And now we're going to, step 1 is create the model. Now, if you scroll back up, you'll see that our best performing model is, or maybe you just remember, was insurance model 2. Now, if we get a summary of what that was, insurance model 2.summary, we're going to just reproduce the same model. Oh, another typo. But this time we're going to call it, so there we go, 3 layers, 1 dense of 100 units, 1 dense of 10 units, and the output layer of 1 unit. So let's reproduce this, and we'll make it insurance model 4 equals tf.Keras sequential, and we'll come right to the start. We'll go tf.Keras layers. We'll add the first hidden layer to our model with 100 hidden units. tf.Keras layers dense 10 and tf.Keras layers dense 1. There we go, we reproduced that. Now, what's the second step when we're creating our models? Step 2 is to compile the model. So we'll take insurance model 4 tf.compile, and the loss function is going to be tf losses.mae, and the optimizer is going to be tf optimizers. We're going to use Atom because that's the same optimizer we use for Model 2. And then we can go metrics equals MAE. Beautiful. Now, number 3, here's where the different part is going to be. So Insurance Model 2, we fit it on, if you scroll up, you can check it out, on unnormalized data. So we just fit it on X-Train, only with one hot encoding, but not normalized. So to change the experiment, here's where we put on our experimenter hat. When we're running these experiments, we're just changing one small thing at a time. So the thing that we're changing in this experiment, Insurance Model 4, is the data we're using. Everything else remains the same. X-Train normal, because we want to see, but it can still fit on the same labels. And we want to fit for the same amount of epochs. So we can still see, we only change one little parameter here, so we can see how that influences our model. Now you're ready? And go. Beautiful. Training is going to be nice and quick. All right. Okay. MAE 3636. Now we're going to evaluate our insurance model trained on normalized data. So we got insurance model 4.evaluate. Let's get it on. Now we have to evaluate it on the same type of data it was trained on. So that's an important point too, is because we trained it on normalized data, we have to evaluate it on normalized data. Shift and enter. Insurance, I keep typing N before A. There we go. How did it go? Okay, 3438. Now if we come back up to our insurance model 2, which was the best performing model so far, where was that? So there's insurance model 3. All right. So that didn't do too well on the test data set. Now, what we're after is insurance model 2. Oh, look at that. Evaluating the larger model. So if we copy this, let's copy this so we can compare our other model. If we were doing this properly, we might have saved the results of insurance model 2 to a variable, so we didn't have to go up and copy this. But let's make a code cell. So this is insurance model 2. Insurance model 2 results. Look at that. What a reduction. So that's 5,000 MAE. Just by normalizing our data, we've gone from 5,000 MAE to 3,500 MAE. That's incredible. That's a reduction of like 30% or so. So now I hope you're starting to see the benefits of all of the different hyperparameters we can tune with our model. So not only can we tweak how we construct our models, how we compile them, how we fit them, we can also tweak the data that we pass it to them. So if we come back and look at our keynote, this is what we've done. We've done the scaling type. All we did was we convert the values or the target features that we wanted to convert to be between 0 and 1. That's all we changed. And we did that with about 10 lines of code here. And those 10 lines of code saw a reduction in error of about 30%. How cool is that? So that's the experimenter mentality that I want you to start developing throughout the rest of this course, is that the first result you get when you build a neural network model it's definitely not your last result, because there are lots of different things that we can tweak. We can tweak the model, we can tweak the data. We're going to have a lot more experience with this going forward, but that's one of the main benefits of normalization, is we see a faster convergence time. What that means is that our model gets to a better result. I mean, if we trained insurance model 2 for longer, say for 200 epochs, it might have reached this error rate here. But when we normalize our features, our models tend to converge faster. In other words, they get better results faster in less epochs. So, again, normalizing data doesn't guarantee improved results, but it's something worth trying because of how easy it is to implement. And in fact, in a lot of our pre-processing code that we do going forward, normalization will be built in, such as when we're dealing with images. Alrighty. So I think we have covered well and truly enough for neural network regression with TensorFlow. Have a look at this. Look how far you've come. You should be incredibly proud. We started by creating data to view and fit. We dealt with input and output shapes. We went through our steps in modeling with TensorFlow. If we come back, this big boy here, look at that. We went through all of these different steps. How cool is that? Now, we improved our models. We evaluated our models through visualization and evaluation metrics. We've run a whole bunch of experiments. We've loaded and saved our models. And we've even gone through a larger example from an open source data set. So give yourself a pat in the back. I've set up some exercises and extracurriculum activities to go along if you want to test your skills even further. I really encourage you to try out the exercises before looking at the solutions that come along with them. But otherwise, go back through all of the concepts if there was something you didn't really understand, practice it, write a bunch more code, get a few things wrong, see what works, see what doesn't, and I will see you in the next section. Neural network classification with TensorFlow. Now, before we get into anything, what we're going to cover or any code at all, I need to stress something. And that's, where can you get help? I'm going to be writing a bunch of code. Better yet, we're going to be writing code together. So make sure you follow along with the code if you can. Remember our motto, if in doubt, run the code. Don't forget to try it for yourself. If you need the doc string, which is a bunch of information about the functions that we're going to be using. If you're using Google Colab, you can press Shift, Command plus Space, or if you're on Windows, this might be Control. If you're using Jupyter Notebook, it's probably going to be Shift and Tab. If you're still stuck, you can search for whatever problem you're having, and we're going to get a lot of practice searching for our problems as well, because that's what I want to stress. As much as we can teach in this course, you're still going to have to develop the skill of being able to search for answers to your own problems. Now, if you do search for it, you'll probably come across resources such as Stack Overflow, or probably more importantly, the TensorFlow documentation, since we're going to be writing a lot of TensorFlow code. And then after you've searched for it, try again. Rewrite the code if you have to. Look at the examples in the TensorFlow documentation and copy them out by hand and try them in your own notebook. And then finally, this is probably the most important out of all of these steps, is if you're still stuck, ask a question. Don't forget the Discord chat, and that means including those dumb questions that you think you have. All right? The person who asks the most dumb questions gets smartest the fastest. Oh, and actually, I want to add one more to this list, and that's the course GitHub. So if we come to here, GitHub. This is Mr. D. Bourke, that's me, TensorFlow Deep Learning. This will have all the materials related to the course you're currently going through. I'll leave a link. At the moment, it's still a work in progress, but by the time you go through this video, it'll have a bunch more stuff and everything you need. Now, every notebook and concept we go through has a ground truth notebook. So, for this one, 02, Neural Network Classification and TensorFlow, this is the information we're going to go through. In the videos, we're going to be writing all of this code out. However, the notebooks here, so this one in the GitHub, have a lot more text around the code that we're writing. So if you want a more text-based explanation to go along with the videos and along with the code, so say in the video we just write this code, if you want all this annotation around it, be sure to check out the TensorFlow Deep Learning GitHub, and that'll have all the information you need. So without any further ado, let's get back to our keynote. And since we're covering neural network classification, you're probably asking yourself, what is a classification problem? Well, let's have a look at some example classification problems. The first one is binary classification. Is something one thing or another? Now, an example of this would be asking the question, is this email spam or not spam? That's actually probably a trend you'll see in binary classification. Is this thing something or not something? So here, we've got clearly a nice email to my email there, daniel@mrdbourke.com. Hey Daniel, this deep learning course is incredible. I can't wait to use what I've learned. Oh, thank you so much. That's a beautiful email. I definitely want to see that in my inbox. So we might train a machine learning model or a neural network to classify this text as not spam. And then if I have this email here, which is, again, to my email, daniel@mrdbourke.com. Hey, Daniel, congratulations. Oh, that's a 1. A bit of a typo there. You win a very large sum of money. As much as I'd like that large sum of money, that's probably spam, and I don't want to see that in my inbox. So that's binary classification. Now, another very common classification problem is multi-class classification. This is where you'll have a question such as, is this a photo of sushi, steak, or pizza? So we have a photo of sushi, we have a photo of a beautiful, delicious steak, and then a delicious pizza. Now, multi-class, as you might have guessed, is more than one thing or another. Now, we've got 3 classes here, sushi, steak, pizza, but in multi-class classification, we could have 100 different classes or 1,000 different classes, but the principle would still remain. Is this a photo of, so we had 100 different foods. Maybe we added over here a sandwich. So the principle would still remain. There's multiple different things that these photos could be of. So multi-class classification not only relates to different photos of food, it could be different photos of cars, it could be different photos of animals, anything you could imagine. And finally, another very common classification problem would be if you are asking, what tags should this article have? So here we have the deep learning article from Wikipedia. Now, maybe you want to, if you're Wikipedia, you want to sort your articles, because you have millions of them, into different categories. And so just labeling it with one category, such as deep learning, may not be enough. You want to relate it to other things such as machine learning or representation learning or artificial intelligence. So in this case, multi-label classification. Now, these two are going to be pretty confusing to begin with. You just need to figure out a couple of example problems to sort of start to understand them. But I know when I first started deep learning, I often got multi-class classification and multi-label classification mixed up. But the easiest way, or the way I remember multi-label classification, is that there's multiple label options per sample. That means that this one sample, this one article here, could have 3 different tags, or it could have 5 different tags. Whereas in these photo examples in multi-class classification, we only want one label per sample. So we have one photo, and the one label would be sushi. One photo, one label would be steak, and so on for pizza. Whereas in multi-label classification, we have one sample and multiple labels. So now that we've had a look at some of the most common classification problems you're going to come up against, binary classification, multi-class classification, and multi-label classification, let's have a look at the things we're going to cover, or specifically the things we're going to write code for. So here's what we're going to cover, broadly. Now I say broadly because these are just subheadings. What really matters is what we actually write code for. So we're going to look at the architecture of a neural network classification model. We're going to see the input shapes and output shapes of a classification model. In other words, the features and labels. We're going to look at creating custom data to view and fit. We're going to go through the steps in modeling, such as creating a model, compiling a model, fitting a model, and evaluating a model. We're going to see what different classification evaluation methods we have. And then finally, once we've trained some models, we're going to look at how we can save them and load them. And how are we going to do that? Well, we've seen this before, but we'll see it again. We're going to be cooks, not chemists. Cooks are very experimental. They try a whole bunch of different things, and they might measure something a little bit, but they're also going to just, if a recipe isn't going exactly how they want it, well, they're going to improvise. So that's what we're going to be doing. We're going to be cooking up lots of code. So now we've covered some example classification problems and what we're going to cover. In the next video, let's check out what the inputs and outputs of a classification model might look like. So, let's say we're working on a classification problem. And we saw this before, the idea of taking some photos, and then perhaps we're building an app that we want to be able to take a photo of whatever food we're eating and classify it as sushi, steak, or pizza. That's the app that we're building. What might our inputs and outputs look like? Well, we've kind of already got them here. Our inputs are going to be some kind of image of food. And then our ideal output, something over here, will be, if we took a photo of this one, we want it to be sushi. And if we took a photo of this steak, we want it to be steak. And then if we took a photo of pizza, pass it through our app, the ideal output would be pizza. Now, what might this look like in practice? So, all right, well, here's our little scenario here. This is our machine learning algorithm that we might build, or deep learning algorithm. And we've already discussed what our inputs are and what our ideal outputs are. But what's the rule that we have to, before we can pass our inputs to our machine learning algorithm, or better yet, what does our machine learning algorithm like to look at? Can it understand photos straight away? Like if we just took a photo and just said, hey, machine learning algorithm, tell us what's in this photo. Will it be able to do that? Well, if you remember from a previous section, what do we have to do to our inputs before we pass them to our machine learning algorithms? Oh, maybe this is a little inkling. So if you're not sure, that's perfectly fine. But what this is so if we have a photo, let's say we already know what the width is and what the height is. So it's 224 by 224. So this is a square image. Now, what are we moving towards? We're starting to numerically encode what an image is. So we're starting to break it down from being just an image to being, okay, this is a 224 by 224 image. All right, we know a little bit more information about our image. So we know the width, we know the height. Oh, and what's C? We might know the color channels. So that's 3. So C equals color channels, red, green, and blue. So we might know that some combination of red, green, and blue pixels in 224 by 224, some combination of those different color values are going to give us this image of sushi. And the same thing for steak, and the same thing for pizza. Now, these width and height are arbitrary, but very often you'll change your numerical inputs of a machine learning model to have all of the same width and all the same height when you're dealing with images. So what might we do before we pass these inputs directly to our machine learning algorithm? Well, we're going to turn them into a tensor. In other words, a numerical encoding. Now here, we've got normalized pixel values. So that means we've changed them to be whatever they were in terms of red, green, and blue, to be some value between 0 and 1. We're going to see this very hands-on in upcoming videos, so don't worry if this isn't making sense. The concept here is that we have images and we have to turn them into numbers in some way, shape, or form before we can pass them to our machine learning algorithm. And then our machine learning algorithm often already exists if we're using something like transfer learning. If not, we can build our own custom one. And then we pass it through. The machine learning algorithm is going to learn patterns in the data and then create some prediction outputs. So let's see here. What have we got? Okay, we've got another tensor, and it seems that the highest value here is highlighted for sushi. All right. But we get 0.00 for steak and 0.03 for pizza. Is that the first image? So that would be correct. Okay, that's great. But then this second image, the one of the steak, the highest value, it predicted sushi. And then these two values are lower for steak and pizza. So that would be wrong. This one, okay. So 1 out of 2, not too bad. And then this final one here, say this is for the pizza image. Same process again, turn it into numbers, pass it to our machine learning algorithm. And then it's got a predicted output here of 0.03, 0.07 for steak, and then 0.09 for pizza. So the highest values for pizza. And so that would be correct. Wonderful. Now, how does it generate these? Well, if we have a look, what are the actual outputs that we were looking for? In our case, we're building an application to classify different images of food. We take a photo of food, We run it through our machine learning algorithm, and then the ideal output is, for this photo is sushi, this photo is steak, and this photo is pizza. So, if we wanted our machine learning algorithm to be able to create predicted outputs like this, perhaps we can show it lots of different examples of images and their ideal output. Okay, so this is the premise of neural network or machine learning classification. This is our inputs over here. We numerically encode them, pass them to our machine learning algorithm, and then have some sort of output. All right. So the example we've seen here is for multi-class classification because there's one or more, each image or each sample can be one or another class. However, this premise of taking some sort of samples, numerically encoding them, passing them to a machine learning algorithm, and then have some sort of output, goes for all different types of classification inputs and outputs. So now we're familiar with the high-level overview of what a classification inputs and outputs will be. Let's have a look at what the shape of these tensors would be, because that's another very important point, as we'll see in practice later on. But before we do so, I want you to have a think about, if we've got these inputs, what might the shape of our input tensor be? And if we've got these outputs, or these ones here, what might the output shape of our output tensor look like? Have a think about that, and we'll cover that in the next video. Welcome back. In the last video, we checked out an example multi-class classification problem, or in other words, the inputs and outputs of what that type of problem may look like. So we had some images here, food images, and we wanted to take a photo of them and classify them as what's in that image. So in our case, we had sushi, steak, and pizza. We learned that no matter what classification inputs we have to numerically encode them in some way. So for an image, we grabbed the pixel values. So we learned that the width was 224, the height was 224, and there was 3 different color channels, red, green, and blue. And we figured out that we can turn those into a tensor and pass that to our machine learning algorithm. It's going to figure out some patterns in these input tensor or in the input images, and then create some predicted output that's based on looking at lots of actual samples of image to label pairs. So knowing that our inputs are in the form of a tensor and the outputs are in the form of a tensor, let's now have a look at what the input and output shapes of those tensors are, which is a very important concept. Because we're working in TensorFlow, all of our data is going to be contained within tensors. Inputs and outputs of our neural networks, of our deep learning models, of our machine learning models are all in tensors. And if they're the wrong shape, well, we run into errors. So this is for an image classification example. We're continuing off with what we just saw. We have our little setup here. Inputs, machine learning algorithm, outputs. We have our image of food, in this case is just the sushi one, and we know that the width is 224 and the height is 224, and there's 3 color channels, red, green, and blue. So what we might do is numerically encode this, pass it as an input to our machine learning algorithm, and it's going to output some kind of prediction probability. We haven't covered this, but we will see this in code later on. This is just more so the concept. Now, the reason why there are 3 options here is because we are building a multi-class classification image classifier, where the output could be sushi, steak, or pizza. And in this case, our machine learning algorithm has got this one correct because the highest value is for sushi. And that's what the input image is. Now, let's check out what or how our image would get represented as a tensor. So here we go. These might be the dimensions of our input tensor. Batch size, something we haven't covered yet, but that's all right. We'll see that coming up. Width, height, color channels. We have covered these. So the width here is 224. The height here is 224. And the color channels would be 3 for red, green, and blue. Now, the shape of this tensor will be, for batch size, might be none, 224, 224, 3. Do you see how the the width value goes into here, the height value goes into here, and the color channels go to here. Or we might have a shape of 32 for the batch size, 224 for the width, 224 for the height, and 3 for the color channels. Now I've set 32 here because 32 is a very common batch size. All you need to know for now is that oftentimes when we're training a machine learning algorithm, depending on how much data we're working with and depending on the size of the computing chip that we're working with, it may only have enough memory to look at 32 samples at one time. So say we're working with 10,000 images, which is very common in image classification. Our machine learning algorithm may only look at 32 images at a time so that it doesn't run out of memory. And again, the reason why it's none or 32, 32 is very common. I think it's actually the default batch size in TensorFlow, but none is because this could be an arbitrary number. And it's important here that the width of this image isn't set at 224 and the height isn't set at 224. But again, these are very common values you're going to come across. So that might be what our input tensor shape looks like for a single image. Or if we have a batch of 32 images, it might be of this shape. And then if we have a look at our output, the shape of this might be 3 because we're dealing with multi-class classification and we have 3 potential classes. So that's the shape of this output tensor. Now, of course, this is for our image classification example. However, these shapes will vary depending on the problem you're working on. So say what if we had 10 different types of food here? What do you think the output shape would be? Well, it might be 10. And say this image was 300 by 300. What might change here? Well, the width and the height might change to 300 and 300. So we're going to get very hands-on with this going forward, but this is just to demonstrate conceptually what we have to do for our classification problems to work on them with deep learning and machine learning algorithms. We have to take our data, numerically encode it into some way, which is typically represented as a tensor, and because we're using TensorFlow, it will always be a tensor. And then the same with the output. Depending on what outputs we have to define them as some sort of tensor, and they will typically have a shape dealing with the number of classes. If you're working on multi-class classification, that is, the output shape will have the same number, or will be the same number as the number of classes we have. But again, this is just a conceptual overview. It'll start to make a bit more sense once we start to build classification neural networks. And speaking of which, let's have a look at that in the next video, what the typical architecture of a classification neural network looks like. Welcome back. In the last video, we had a look at what the input and output shapes of an image classification example might look like. And remember, this is specifically for an image classification example. These may change depending on the problem you're working on. So say we were working on text classification. Your input shape may differ to be the number of words in a string. So it may be 32 and then 100 for 100 words, and it won't have these dimensions over here. It'll just be one number for each word in that string. And then the same over here. Say we just wanted to classify an email as spam or not spam. We may have an output shape of 2. Again, lots of practice coming up, but just keep in mind, one of the big things for classification problems is defining the input-output shapes of our machine learning or deep learning algorithms. So now, speaking of those, let's have a look at what the architecture of a classification model might look like. We've got a little spoiler alert here. Here's some TensorFlow code. We've been very familiar with this in the regression section. However, we might notice a few different things. Oh, we've got input layer. All right. We've got activation. We haven't seen much of that. We've got another activation here, softmax. All right. What else is different? We've got loss. Okay. So we're familiar with these steps. 1, 2, 3, 4. The main differences you might see here is the loss function and the input shape and the activation. We haven't been hands-on with those just yet, but throughout the classification section, as you might have guessed, we definitely are going to be. So now, it's important to note that this is a typical architecture of a classification model, and we're going to building lots of these. So although I'm giving you sort of a guideline as to what these architectures may look like, they definitely vary depending on the problem we're working on. However, this is pretty universal. And again, this is adapted from page 295 of the Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow book by Aurélien Guérin. Highly recommended that book. It'll be in the extra curriculum section of this course. So let's take a look at what's going on here. We have hyperparameters, and remember, a hyperparameter is something that we can adjust ourselves as developers. And we might have a binary classification problem and a multi-class classification problem. Now, note here, we haven't got multi-label classification. However, multi-label classification architecture is often very similar to a multi-class classification. So let's start with the input layer shape. If we go here, and all of these colors are going to activate for me automatically, aren't they? But that's all right. We'll step through it one by one. Input layer shape. We have here tf Keras input. So here's where we're defining the input layer shape. Do you remember in just the previous example we looked at before? It might be the same number of features, e.g. 5 for age, sex, height, weight, smoking status in a heart disease classification problem. But we looked at an image classification problem. So here we might have the input shape of a particular image might be width, height, number of color channels. So that's what our image looks like in tensor form. Again, this shape will change depending on the problem you're working on. Now for multi-class classification, it's going to be the same thing as binary class classification. Now hidden layers, again, this is plural on purpose. We've got one here, and this is problem specific, what you set this to. The minimum is going to be 1, the maximum is unlimited. So I think we're actually going to be working with a neural network with over 100 layers. That might be in this section or a later on section, but this one just has one hidden layer there. And for multi-class classification, we can look at the same value here. It can be 1 or up to unlimited. Neurons per hidden layer, that's this green value here. Problem specific, generally 10 to 100. Again, this can wildly vary depending on what you're working on. In our case, we've set 100 here to the hidden layer. And for multi-class classification, we've got same as binary classification. Now the output layer shape. For binary classification, it's going to be 1. So remember, binary classification is something one thing or another? Is this email spam or not spam? So we want the output layer shape to be 1. And multi-class classification is going to be 1 per class, e.g. 3 for food, person, or dog photo, if we were working on an image classification problem to decide whether a photo was of food, of a person, or of a dog. And that's the value we've put here, 3. So in our case, this input shape might actually work for this problem here. This output shape. But the input shape would also work because it could potentially, if these images, so the images of food, of a person or a dog, were 224 pixels wide, 224 pixels high, and had 3 different color channels. Once we'd turn them into tensors, of course. Now we have here the hidden activation. So this is the hidden layers. So the activation function that we have within the hidden layer. So it's often defined with the activation parameter. Now it's usually ReLU, which is rectified linear unit. We haven't seen that before, but if you want to go ahead and do a little bit of research before we get into coding, feel free to look up ReLU. And again, same for multi-class classification. We're going to use now again, there are multiple different hidden activation functions, but I say usually ReLU because that's what you're going to see very often, and that's what we're going to be using throughout the course. Now, output activation. This is the activation function in the output layer. Again, a concept we haven't really covered so far, but I'm just making you aware of what the names of these things are. So for binary classification, we're probably going to be using a sigmoid activation for our final layer. And for a multi-class classification problem, we're probably going to be using a softmax activation, which is what we've got here. All right, so this architecture looks like it's for multi-class classification. Now, loss function. Across the board, we're going to be using cross-entropy, which is a loss function for classification problems. Now, for binary classification, we're going to be using binary cross-entropy in TensorFlow. And for multi-class classification, we're going to be using categorical cross-entropy in TensorFlow. So it looks like here, when we compile our model and define the loss function, we've used tf.Variable losses categorical cross-entropy, which makes sense because we discussed before that this is a multi-class classification architecture. And as for the optimizer, we're going to use old faithful stochastic gradient descent, or another old faithful is Atom. So actually, I think we might test out both of these, but I think we're probably going to be sticking with Atom because Atom is safe. And then we go here, multi-class classification, same as binary classification. All right. So that's a typical architecture of a classification model. Again, a lot of things here that we haven't necessarily covered, but we are going to be getting hands-on building a lot of these. And I think that's what we've got here. Yeah, we're going to be building lots of these bad boys. And the reason you might be wondering why I said Atom is safe, I want to reveal that. So let's go here. Andre, here's another external resource, neural network recipe. I'll put this in the extra curriculum. A recipe for training neural networks. So this is by Andre Karpathy. If we go here, Atom. A few tips and tricks for this stage. Atom is safe. In the early stages of setting baselines, I like to use Atom. He's talking about the Atom optimizer. With a learning rate of this, Atom's learning rate is actually very good in TensorFlow. It's default 1. In my experience, Atom is much more forgiving to hyperparameters, including a bad learning rate. For convnets, a well-tuned stochastic gradient descent will almost always slightly outperform Atom. So again, a lot of things here you might not be aware of, but just know Andre Karpathy is saying Atom is safe, and if you're wondering who Andre Karpathy is, let's go to About, see my website. I am the Senior Director of AI at Tesla. So Andre knows his stuff about deep neural nets. So if Andre says Atom is safe, we're going to trust him. But anyway, actually, let's be skeptics. Let's not trust Andre and let's test it out for ourselves. So in the upcoming videos, we're going to get... Oh, actually, I had a little demo of what was happening here. So here's our inputs. They get encoded into tensors of this shape. And then here's our outputs. So that completes that slide. But with that being said, we've talked enough. Let's code. Let's code. Now that we've looked at what a classification problem is, what some tensor input and output shapes might look like, let's get hands-on and start to code some classification code. We're going to start a new notebook at Colab. Wait for this to load up. Beautiful. Now I'm going to call this one O2 neural network classification with TensorFlow. And I'm going to add the video tag so that you know, once you see this notebook in the GitHub, that this notebook was made during the recording of videos. Remember, we've got in the GitHub the ground truth version of this notebook. Doesn't have the video tag on the end here. But we'll get out of that. So let's write here. Introduction to neural network classification with TensorFlow. So in this notebook, we're going to learn how to write neural networks for classification problems. And remember, what's the definition of a classification problem? A classification problem is where you try to classify something as one thing or another. And there's a few types of classification. You've got binary classification, multi-class classification, and multi-label classification. And we've got here a few types of classification problems. Now, we'll turn this into Markdown. I'm going to press Command MM. You might press Control MM if you're on Windows. So we've got a little intro here. Now, the first thing we might have to do is, before we can write any code, is we need some data. So how about we write a title here, creating data to view and fit. Now, there's a lot of toy classification data sets out there, but I always like creating our own and getting a model to work on our simple data set before moving on to an actual problem. So it's like a rehearsal experiment before our actual experiments. How about to make some data, we can go from sklearn.datasets, import make circles, and then we'll go here. We want to make 1,000 examples. So we want 1,000 different samples of data, and we can create circles. Oops. And samples equals 1,000. And then if we should go down to here, create circles, x, y equals make circles, and samples. Again, you could change this to 10,000 if you wanted to, or 100. I'm going to stick with 1,000. That's a good number. And samples, noise can be 0.03, and random state can be 42 if you want to make this reproducible, so we have the same data. Now, you might be wondering, Daniel, we've never used make circles before. And you'd be 100% correct. This is the first time we've used this in the whole course. But how do you get help on something if you weren't sure? We want to press Command, Shift, Space. Def make circles. So make a large circle containing a smaller circle in 2D. A simple toy dataset to visualize clustering and classification algorithms. Beautiful. So if we really wanted to figure out what this is how to make example classification data with sklearn. There we go, an introduction to machine learning with scikit-learn, examples. So we've got a few options there. I've just chosen, that's basically what I did when I found out about this make circles function. And there's probably a way to do that in TensorFlow. I'm not quite sure if it's as quick as this one, but if you want to give it a try, once you see what this data looks like, feel free. So now let's check out the features, which is under the X namespace, usually a capital X. Okay, so we have an array here, and let's check out the labels. Check the labels. All right, ones and zeros. So we've got two options here. I'm guessing one of these samples here, so this is a sample, has this label, number 1. And another sample further along here, say this one, has this label 0. We might just make this a bit smaller. I'll check the labels, that's what we want there. So if we have two label options and we're working on a classification problem, which one of these three are we working on? Is it binary? Is it multi-class? Or is it multi-label? Well, it's not multi-label because each one of these has one label. So each sample has one label. And it's not multi-class because there's only 1 or 0. So this is a binary class classification problem. But if we're looking at our data like this, I mean, I could look at this. I've used this before, so I kind of know what this means. But if you're looking at this for the first time, it might not make sense. So what's our Data Explorer's motto? Come back to the keynote. The machine learning, or even the Machine Learning Explorer's motto. Visualize, visualize, visualize. And what's the first thing we should visualize? The data. And we could visualize the model, the training, predictions. And it's a good idea to visualize these as often as possible. So let's see how we might visualize our data. Let's write ourselves a little note. Our data is a little hard to understand right now. Let's visualize it. So to get it into a structured format, I'm going to import pandas as PD. And then I'm going to turn it into a data frame called circles. PD.dataframe. And I'm going to label it x0 for this element here, or this sample here. And that can be x, all of the items in the 0th axis. And then x1 can be x. We want all of the items in the first axis. There we go. And then we want the label column to be y. There we go. And let's look at our circles data frame. Typo there, of course. Circles. Beautiful. Okay. So now this is a little bit easier to understand as it is. We've got x0, x1. So we have 2 features per label. And so this coordinate 0.754246 and 0.231,481 has the label of 1, and so on, times 1,000, because we set n samples to 1,000. Now, this is still a little hard to understand. I wonder if we can visualize this with a plot. Let's try that out. Visualize with a plot. So how might we do that? Import matplotlib. I like to visualize as much as possible before I start writing neural network code. plt.scatter. We want a scatter plot. Scatter plot's a very good plot. We want to just plot this. And the color can equal y. And the CMap can equal, this is just the color layout. I want it just to be red, yellow, blue. I think that should do. Let's have a look. Oh, look at that. Now, so, seeing this, if we read the docstring of make circles, has it done what it says it's going to do? Make a large circle containing a smaller circle in 2D. I think it's done that. We have a large circle and a smaller circle. Now, from this plot, can you tell what type of model we're going to build? It's okay if you can't, but I just guess. Like, what are we trying to do here? What would we try to do? I'm giving you a little hint here by running my pointer in between the 2 circles. How about we build one to classify red or blue dots? So in other words, we want our model to potentially draw a line right through the middle of these 2. So if we were trying to predict on another 100 rows, and we had values like this, would they be a 0 or a 1? Would they be red or blue? Now, I want you to think about, before we go ahead, this is just a conceptual thing, what is the difference between the data we're looking at here and the data we've looked at in our regression notebook? So if we start a new tab, what is a regression problem? And then if we went to images, what's the difference between this data here and this data here? So have a think about that. Just look at this, like Google regression problem, check out the images, and just have a think. What's the major difference between our 2 types of data here? And one more thing before pushing forward, so that's your challenge, just to compare these 2 types of data. I want you to have a look at TensorFlow Playground. Oh, .org, not .com. Here we go. Tinker with a neural network right here in your browser. Don't worry, you can't break it. We promise. So again, we've got a little few options here over what data set we want to use. And what's this one look like? I mean, we've got a few. Watch them change over here. We've got this one. What's the similarities between this data set and this data set? So your 2 exercises before the next video is to compare this one here. You might have already done that because we've talked about it enough. And then the other one is to spend 10 minutes at playground.tensorflow.org playing around with all the different parameters here. Try changing the learning rate, the activation, the regularization. Doesn't matter if you're not sure what these things are. Press play. Change the number of hidden layers here. Change the number of neurons. And see what happens with this data set here. So give that a try, and I'll see you back here in the next video. How'd you go? Did you play around with the neural network playground? I've just added a little exercise here with this hammer and spanner emoji. If you ever see that throughout the course, that's an exercise. So before pushing forward, spend 10 minutes playing around with the playground tensorflow.org, building and running different neural networks. See what happens when you change the different hyperparameters. So if you haven't done that yet, give that a try and then continue the video. But otherwise, we've created some data, we've visualized it. Now, what's another important point is the input and output shapes of our neural network. So let's inspect our data. So check the shapes of our features and labels. So what's our features shape and our labels shape? Wonderful. So we have 1,000 samples of X and 1,000 samples of Y, and X has a shape of 2 because there's 2 samples, whereas Y is just because there's one output. These are scalars, so they don't have a second dimension here. They're just one value. All right. So if we wanted to check how many samples we're working with, is just len X, len Y. And if we want to view the first example of features and labels. So again, we're just becoming one with the data here. We're really just familiarizing ourselves with what we're trying to do. We've already seen a few of these things, but just for completeness, we're putting this here. So okay, we've got 2. Here's what we're trying to do. We're trying to take this point, feed it to our neural network, and generate an output, something like this. And let's say, can we get another one with a 0 label? Are we going to get a 0 label? Nope. I believe the 5th one may have been. No. All right. So some of these values here for X have a label of 0. That's all you have to know for that. Now, we've checked the input and output shapes. What might be the steps or the next steps? So steps in modeling. We've practiced this with our regression problem. So now that we know the input and output shapes, how might we build a neural network to classify whether something is a blue dot or a red dot? So how about we go back to our keynote here and steps in modeling with TensorFlow. We reveal our beautiful, colorful picture. Step 1 is get data ready, turn it into tensors. Well, we kind of have that, except they're in NumPy arrays at the moment. But remember, NumPy arrays work beautifully with TensorFlow. So we'll say that we've finished this one. Now we have to build or pick a pre-trained model to suit our problem. Well, in our case, we're going to build a model. So we have step 1, create a model specified to your problem. We might have to define the input shape here, or sometimes Keras layers can automatically infer the input shape. Then we might have a hidden layer and an output layer. What would our output layer shape here be? If we come back, we only want to predict whether it's one thing or another. If you remember back to the slide where we talked about the typical architecture of a classification problem, that may give you a hint because we're working with binary classification. Then we want to compile the model. That's step 2. I nearly said fit the model, but we have to compile it after we create it. Remember step 2, Daniel, come on. Now, if we're working on binary classification, what might our loss function be? What optimizer could we use? What metrics could we use? And then once we fit the model, okay, that seems like we've got that set up. We've got X and Y. Well, we haven't got a training data set actually, have we? Or a testing data set. We might just stick with X and Y for now. All right, so now we've got the steps here, 1, 2, 3, 4. I'm going to issue another challenge. We've got X and Y. See if you can create a model with what we've learned so far. Refer back to the slide where we talked about the architecture of a classification model. And write some neural network code with TensorFlow. Give it a go. And I'll come back in the next video and we'll write a neural network classification model together. So in the last video, we checked out what the input and output shapes of our data may be. And we also had a brief overview of what the steps in modeling with TensorFlow are. So how about we start to implement those? So remember, the steps in modeling number 1, or the steps in modeling with TensorFlow are typically 1, create or import a model, 2, compile the model, and 3, fit the model. And then the fourth one is evaluate the model, etc. 5 is we usually here will tweak, 6, evaluate, etc., etc. Tweak, evaluate, tweak, evaluate, tweak, evaluate. But let's focus on these first 3. We'll get these first 3 done for our classification problem. So how about we start, set the random seed, tf.random set seed. Now what's the simplest model we could start with? How about we just start with one hidden layer. We'll go create the model using the sequential API. So we go model1 equals tf sequential, and then we'll add a single dense layer. Wonderful. And then what's step 2 after we create a model? We have to compile the model. So model1, because compile. Here's where it's going to be different from the regression models that we've built. And now, before I write the code, I want you to refer back to this slide here, the typical architecture of a classification model. Where are we up to? Well, we're compiling a model, and we have to define the loss function and the optimizer. So if we look back at what we're working on, what are we working with? Are we working with binary classification or multi-class classification? Come back to our problem. What does it look like? Red or blue dots? So it is binary classification. So what might our loss function be? Before I write it in here, I'd like you to give it a try. Have a look at this and see what it might be. Did you give it a go? If not, that's all right. Let's write it down. Loss equals tf losses dot binary. Is this going to autocomplete for us? Cross entropy. I believe it might be capital E, but we'll find out in a second. It'll error for us. Now the optimizer. What optimizer do you want to use? tf optimizers. We come back to our typical architecture of a classification model. We can use SGD or Atom, or really there's actually a plethora of optimizers we could use, but these two are the most common you'll see in practice. We'll start with SGD. And the metrics is going to be, we haven't looked at classification metrics yet, but we'll get very familiar with them. Actually, what would you do if you wanted to know different classification metrics? I've put accuracy here, that's a bit of a spoiler, but let's go how to evaluate a classification model. Here we go, evaluating a classification model. What does this tell us? Richie NG. Oh, look at this. Topics. Review of model evaluation procedures, model evaluation metrics. Okay. Model evaluation metrics. Boom, classification. Classification accuracy. There are many more metrics and we will discuss them today. Classification accuracy. All right, beautiful. So then we got a few more options. We could keep going through that if we wanted, but we're just going to stick with accuracy for now. And accuracy is just basically out of 100 examples, how many did our model get right? So what percentage? And now if we go here, and we want to, well, step 3, fit the model. So we have model1.fit, we have X and Y, and we're going to fit for maybe just 5 epochs. So we got the first 3 steps here. And all we've done is we've just followed this. The architecture of a classification model. We've just implemented this in TensorFlow code. So we're ready to run this. Hopefully there's no errors. 3, 2, 1. Oh, TF is not defined. That would help if we imported TensorFlow. Did you catch that? Let's write some code here. We'll get rid of this. We want to import TensorFlow. Can't write TensorFlow code without TensorFlow. Import TensorFlow as TF and check our version. By the time you watch this, your version might be higher than mine. Right now, I'm running 2.3.0. As long as you've got 2 point something, all the code should work in here. And let's see if this runs. We got this wrong. So what is it? Tab. We want, is this going to autocomplete for me? So maybe it's just a little e, and I think this is on the end. There we go. Fits nice and quick because we're only working with 1,000 samples. But what's our accuracy? 48%. This is percentage, by the way, because we've set up accuracy here. So that's saying that on average, out of 100 examples, our model only gets 48 right. Now, what does that tell you? If we're working with a binary classification problem, so we're trying to predict whether something is one thing or the other, basically heads or tails, and our model is only 48% accurate, it's basically guessing. So it's just going up here. It's looking, we have red or blue, and 48% is basically 50%. So it's just going red, blue, red, blue, red, blue, red, blue, red, blue, and you'd get about 50% correct. Well, that's not very good. How might we improve it? What are some steps to improve our model? I got an idea. How about we train it for longer? So let's try and improve our model by training for longer. So we come here, model1.fit. We can just take it straight away. And epochs equals, let's do another 200. And this time we'll turn verbose to 0. So 200 epochs should be enough for our model to figure out the patterns in our data. We've only trained for 5. Let's really step it up. Model1.evaluate x and y. Maybe you're going to catch what I'm doing wrong here. We'll reveal that after. But if you have a look at what we're doing here, fit and evaluate. I'm doing a cardinal sin right now, but that's all right. This is just to exemplify what's going on. Let's see what happens. So it took a little while longer to fit because we're training for 200 epochs instead of 5, but we ran evaluate and now we have loss. So the loss is 6935 and the accuracy is 5 or 50. So 0.5 times that by 100, that's 50. Only 50% accuracy and we trained for 200 epochs. What is happening? Okay, I know how we can really step things up. What if we added another layer and trained for longer? Yeah, that's a great idea. Our model is performing as if it's guessing right now. Let's write that down. Since we're working on a binary classification problem and our model is getting around 50% accuracy, it's performing as if it's guessing. So let's step things up a notch and add an extra layer. Yeah, that worked in our regression problem. It should surely work here. So we'll set the random seed, tf.random.setSeed, and we'll go to step 1, create a model, this time with 2 layers. Model 2 equals tf.Keras sequential. Open up the brackets there, square brackets and curly brackets, tf.Keras layers, dense. Woohoo! This data set ain't gonna know what hit it. Binary classification, 2 different types of labels, 2 layers. And now, what do? After we create a model, we have to compile the model. I'm gonna go model2.compile. What's our loss function? tf.Keras losses, because we're dealing with binary classification. It's binary cross entropy. Little quiz. What would it be if we're dealing with multiclass classification? Optimizer, we're going to keep the same. We're going to use SGD, stochastic gradient descent, and the metrics we're going to set to be accuracy. Oh, this is going to be so much better. Fit the model. All right, model2.fit x, y. By the way, if you already guessed what we did wrong up here, we fit on the same data that we evaluated on. What should we ideally do? We should fit on training data and evaluate on testing data. But, well, because we're working with a toy problem, we're allowed to fudge what we're doing a little bit here. And now epochs, What should we do? Maybe 100. That should be enough. We've got 2 layers. I mean, this model should be great. Ready? Let's run. Now, number 4 can be evaluate the model. Because we set verbose equal to 0, we don't have very much output, but we should have a trained model 2. Evaluate, again, evaluating on the same data we trained on. Not ideal, but in our case, we're just trying to see if our model's learning anything. What? The loss is about the same, even with an extra layer, but the accuracy is still 50. So right now, our model is still not even as good as guessing. Like, it's getting 50% accuracy. Like, you could do that if you just, for every sample, if you had 1,000 samples, if you just guessed, let's see how many there are. Let's go here, code, and circles, label, which is Y, value counts. So 500 and 500. If we just literally went and tried to guess red, blue, red, blue, red, blue, we'd be getting the same results as our current neural network with 2 layers. This is preposterous. What we should do in the next video then is that if our model's still only getting guessing results, we need to pull out a few more bags of tricks to improve our model. So, have a think about, refer to our architecture of a classification model and have a think about some of the things using my cursor in an area that might reveal something to you, by the way. Have a think about some of the things that we haven't yet included in our model and see if you can figure out why our model hasn't learned anything yet. But if not, I'll see you in the next video and we'll see how we can improve our classification model. All right, so we've built a few classification models so far, namely Model 2 and Model 1, which is a little bit further up. There we go. However, we've seen that despite adding an extra layer, Model 2 is still performing very poorly. I mean, it's getting 50% accuracy on our binary classification problem. And since we've got an even amount of samples for each class, so if we look here, we've got 500 samples of number 1 and 500 samples of 0. Now, or 500 samples of a blue circle and 500 samples of a red circle. Now, if you were to toss a coin 1,000 times, you kind of expect about 500 heads and 500 tails. Hence why our model is essentially guessing. So we have to look into our bag of tricks to see how else we can improve our model. So let's look into our bag of tricks to see how we can improve our model. Now, recall back from the previous section where we went through the steps in creating a model, or the steps in building a model, that is. But as you might remember, there are steps from within each of those steps that we can try to improve our model. So if we go create a model, that's number 1. 2 is compiling a model, and 3 is fitting a model. What can we try here? So when we create a model, we might want to add more layers or increase the number of hidden units within a layer. We've seen this. We actually tried this. We didn't increase the number of hidden units for Model 2, but we did increase the number of layers. So we went from 1 layer to 2 layers, and that didn't really improve our model. What else could we do? Compiling a model. So here we might want to choose a different optimization function, such as atom instead of SGD. Now, what optimization function did we use for Model 2? We used SGD, so we might actually, atom could be the next thing that we try there. And then fitting a model. So perhaps we might fit our model for more epochs. So leave it training for longer so that it might get a better understanding of what's going on or the patterns in our data. Now, these steps have just come from, if we refer back, this is what we've been through so far, steps in modeling with TensorFlow. Number one, create a model. We've created a few models here. I want you to think about this one in particular, actually. There's a little part that we haven't quite covered yet, and it may or may not hold the keys to why our model isn't improving, but I'll let you have a think about that before we discuss it. Number two is compile the model. So we define the loss function, in other words, how wrong our model's predictions are. We define the optimizer, which is how our model should update its internal patterns to better its predictions. We define the metrics, which is a human interpretable values for how well our model is doing. We fit the model and we evaluate it. But now if we have a look at how we might improve our model from a model's perspective, we've got a few different ways. Adding layers, we've tried that. Increase the number of hidden units, we haven't tried that. Change the activation functions. We definitely haven't tried that, at least for the hidden layers. Change the optimization function. We could use SGD or Atom or one of the other optimizers in the optimizers package. Change the learning rate. We haven't tried that. Okay, so we've got a fair few things here that we could try. Let's start implementing some of these. And remember, because these are hyperparameters, or because these are changeable, they're called hyperparameters. So if we come back, instead of staring at our slide, let's write some code. How about we increase the number of hidden units? Yeah, and we'll add an extra layer. Let's do that. Set the random seed. So tf random.setSeed. I want to emphasize as well is that if you're thinking, well, Daniel, we don't really have a structure to what we're doing here. We're just trying things and seeing if they work. I mean, you're exactly right in thinking that. And that is a lot of what machine learning and deep learning is. Trying things and seeing if they work. Hence why our machine learning practitioner's motto is, I'm just creating a sequential model here, by the way, and I'm calling it Model 3. But our machine learning practitioner's motto is experiment, experiment, experiment. Now, we've created a first hidden layer here, and we're creating 100 hidden units in this one. So we're stepping it up from Model 2. If I create a new cell, I've turned that into Markdown. I don't want that. You can turn it from Markdown back into code, by the way, by going Command MY or Control MY if you're on Windows. Keras layers dense. Wonderful. And we'll have the final layer there. So if we check Model 2, what we've done here with Model 3 is we've added 10 hidden units to the middle layer, and we've added an extra layer this time with 100 hidden units. So I'll put there, add 100 dense neurons, and this one is add another layer with 10 neurons. All right, this one should definitely work because we've stepped it up a notch here. I mean, if our model with 2 layers didn't work and only 1 hidden neuron, well, it definitely should work with it with 3 layers and over 100 hidden neurons now. Compile the model. So Model 3, compile. What do we have to do for compile? We define the loss function, which is how wrong our model's predictions are. For a binary classification problem, we use binary cross entropy. And then the optimizer. Oh, this time I think we might also change Atom or change to Atom from SGD. Let's try that out. Why not? Metrics equals accuracy, which is a very standard baseline classification metric, but may not be the best one depending on your problem. We'll see other classification metrics in a future video. Oh, 2 equals there. We don't want that. And now we're going to fit the model. Oh, I can't wait to see the results of this one. 3 layers, over 100 hidden units, equals, let's go for 100 epochs. What do we do Model 2 for? I think we only did 5. Oh no, we did 100 as well. So we'll just do 100 this one. Verbose equals 0, so we're not outputting a lot of information. And Shift and Enter. Did we get any errors? No. Beautiful. All right. So let's see how number 4 is evaluate the model. So again, not necessarily a great idea to evaluate on the same data set that we've trained on, but for this toy example, we'll keep it like that. Shift and Enter. What? Bow, bow, bow. What? We're still getting 50% accuracy. We've pulled out our few tricks. We've changed the optimizer to Atom. We've added an extra layer, this time with 100 hidden units, and even another one with 10 hidden neurons. We're still getting about 50% accuracy, so just as good as guessing. You know what we're going to have to do? We're going to have to visualize. What do you think we should visualize in this case? If we want to see how our model's performing and the evaluation metrics are telling us it's not performing pretty well, what's another thing that we can visualize? How about we visualize the predictions? Yeah, I think that's a good idea. So in the next video, we'll make some predictions with our trained model and see, we'll plot them against, where's our graph? Here. Yeah, let's make some predictions on this graph. And we'll plot what our model's predicting, how to separate these blue and red circles. And we'll see what they look like, just so we can understand what our model is trying to, or what the pattern our model is trying to figure out between these two circles. I don't think it's very good. So give that a play around. Maybe you want to try a few more things before we plot those, but otherwise, I'll see you in the next video. In the last few videos, we've been building models to try and classify our toy data set here of blue and red dots. However, they're all performing pretty poorly. As good as guessing. Even we've pulled out a few tricks to improve our models. So what we're going to do in this video is, if we come back to our keynote, and we remember our Machine Learning Explorer's motto, visualize, visualize, visualize. It's a good idea to visualize these as often as possible. We visualized our data, we know what it looks like. We visualized our model, we know the layers and the different components of that. We've seen it train. We haven't plotted a loss curve just yet, but we don't need to because we know it's performing poorly. So let's test out, try visualize some of the predictions that our model is making. Now, how might we do that? We could do it like this. We could go model3.predict x and see what's happening. All right, we get some values there. They're all sitting around, that's a little inkling. They're all sitting around 0.5, but we want them to be closer to 0 and 1. All right, so that's a little inkling there, but I prefer to see things visually. So let's get rid of this. And to do so, what we might do is make a function, a plotting function called plot decision boundary, where what we want is, do you remember with our regression model, we had some data that was like a line, and then we plotted our model's prediction as a line compared to the actual data? Why don't we do the same thing, but with this circular data? Plot our model's predictions against the actual data. So to do so, let's create a function right here to visualize our model's predictions. Let's create a function. I'm going to call it plot decision boundary, because a decision boundary is just basically where's our model deciding where the bounds are between red and blue dots. And this function is going to, that's a better option. So we need to take in a trained model, features, X, and labels, Y. So those are the parameters. And then it'll create, might turn this into Markdown actually. Create a mesh grid. If you're not sure what a mesh grid is, it's a concept in NumPy. So NumPy mesh grid. That's what you can do for anything that you're not sure. Just search it up and have a little play around and figure out what it is. NumPy mesh grid. You could read the documentation there, or we could just practice coding it. Create a mesh grid of the different X values. And then we're going to make predictions across the mesh grid. And then finally, we're going to plot the predictions as well as a line between the different zones where each unique class falls. Now, right now, these steps are all just in English. They may not make sense, So let's start to write code for it. We'll go here, import NumPy as NP, and then we'll create our function, def plot decision boundary, model x and y, and there we go. And then we're going to put in a little doc string here, so we're being nice and Pythonic. So plots decision boundary created by a model predicting on x. Beautiful. So the first thing we have to do is we've taken in a trained model. So there's our model parameter, there's our features, and there's our labels. Now, let's define the axis boundaries of the plot and create a mesh grid. So we want the x minimum and the x maximum is going to be, we can index on x to get both of these values. So we just want the 0th axis, the minimum, and we're going to minus 0.1 to give ourselves a little bit of a margin. And the same thing with the maximum. So we just want the 0th axis, and then we take the max, and then we're going to plus 0.1 to give ourselves a little bit of a margin there. And then we can do the same thing for the y min and the y max, except we're going to index on x and get the first axis. Dot min, the minimum, and the same thing here. Semicolon, 1 dot max plus 1 for a little bit of a margin. Now, if you're not sure what these values are, what can you do for any type of function? You can just take the code, copy and paste it, or probably better to write it yourself, and then xmin to visualize them. This is what we want to look at all the time. Line by line. I'm not going to deconstruct this function line by line, but if you wanted to understand any function, this is what I do. I take the line by line, and then I visualize it in a single cell. So here's the values. These are our boundaries, and now we can create the mesh grid. YY equals, now again, this is coming straight from the documentation here for mesh grid, is np.meshgrid, and then in here it takes linspace. Now how do we figure out what something does? We can do command shift space. Oh, we haven't imported NumPy yet, that's why we can't run this function, or can't get the doc string. We'll import NumPy up there and see what linspace does. Here we go. Return evenly spaced numbers over a specified interval. Okay. So if we did 0 to 10, it might return evenly spaced numbers between 0 and 10. Beautiful. But we want evenly spaced numbers between our x min and x max, because this is going to be the first parameter of our mesh grid. And then we want the same thing for y min, y max. And then we're going to go 100. So here's the minimum, here's the maximum, return 100 values evenly spaced between x min and x max, and create a mesh grid out of this one and this one. If you want to see what that looks like, again, you can copy this and probably put it in a code cell below. Otherwise, let's push forward with the function. There we've created our mesh grid of the different x values. Now it's time to create x values. We're going to make predictions on these. So x in equals np c. Now we want to unravel xx by passing it to ravel, yy, ravel. And if you're not sure what c does, you can go, what can we do? NumPy .c. User manual. Translates slice objects to concatenation along the second axis. So if we pass it in two arrays like this, what does it do? They were stacked and now horizontal. So that's what's happening here. So stack 2D arrays together. Now we're going to make predictions using our trained model. We've passed it in with the model parameter here. So we go ypred, which is our usual variable name for any type of predictions. Model.predict x in. Alrighty. And now we're going to add a little bit of functionality here that we can check for multiclass. We're working with binary classification, but let's check for whether we're working on a multiclass classification problem. This will help make our function usable if we did want to, if we had red, green, and blue circles instead of just red and blue. So we can check the length of ypred for the first sample if that's greater than 1, print doing multi-class classification. And then if so, we have to reshape our predictions to get them ready. Now here we got to go ypred equals np argmax. We haven't seen this before. We could use tf argmax as well. Ypred axis equals 1. Reshape xx.shape. So we're reshaping it just to the shape of xx up here. Now let's make else. If they're binary, we'll print doing binary classification. So this is just the else statement for this little if condition here. And then ypred equals np round. So we're just rounding our prediction. Ypred reshape to xx.shape. Now we're finally up to plot the decision boundary. Again, this function has a fair few steps, but again, if you want to understand it, take them out, deconstruct it, and look at what's happening line by line. That could be some homework for you after this video. Why? I want to contour plot. So what is this? Plot contours. Nice and succinct definition from that documentation there. Thank you very much. But again, we're going to see what this looks like rather than just reading docs. We're going to write as much code as we can. Alpha, wonderful. And we're going to plot a scatter. We need to plot the 0th axis of x and x's first axis. And color this in y. S equals 40. Now what does the S parameter do? Where is S? There, scalar. So the marker size in points. So this will define how big the size of the scatter plot points come out. And then we're going to plot CM, RD, yellow, blue. This is our color. And plot xlim. We want to set the limitations. So this is where XX minimum comes in and the XX max comes in, as well as the Y limitation. We can do the same thing for YY, min, and YY dot max. Whew. Okay, that's probably the biggest function we've written so far. I mean, it almost doesn't fit on the screen. A lot going on here, but now that we've got a function to plot our model's decision boundary, I mean the cutoff point between the decisions it's making between red and blue dots, let's try it out. So we go here, we'll run that. Hopefully there's no errors. Check out the predictions our model is making. So if we want to plot decision boundary, we pass it in our trained model, which is, we'll set model 3 because that's our most recent model. X is just X and Y is equal to Y. Remember, X and Y are just our features and labels. So again, 1 point here leads to a 1 or a 0. We'll get rid of that. You ready? 3, 2, 1. Oh, would you look at that? So, this is why our model is performing so poorly. It looks like it's trying to draw a straight line through the data. Now, what's wrong with this? Well, we've got circular data. So the main issue here is that our data isn't separable by a straight line. But if we were working on a regression problem, what is a regression problem? Now, in a regression problem, our model might actually work because it's drawing a straight line. So how about we test that? We might do that in the next video. And as for this function, if you're wondering, Daniel, like, how did you learn how to create all of this? Well, the truth is, I've borrowed this and I've adapted it for our use case. So if we come here, one of the resources I used was CS231N, Neural Networks Case Study. Now, this is a phenomenal course, Convolutional Neural Networks for Visual Recognition. We haven't actually worked with convolutional neural networks yet. So if you go through this, it might be a bit full on, but I'd highly recommend this, as this is going to be a part of the extra curriculum for this section and the convolutional neural network section. So if we come down here, I dug into the code behind this material here, and I found this. So they've got some spiral data here, and I've just changed it for our circular data. And so I'm going to put this link in here. This function was inspired by 2 resources. Number 1 is this one. And then number 2 was another phenomenal resource, Made with ML. So if we go to Made with ML GitHub, and then into the basics. So this is a phenomenal repo. I highly suggest you star this one. I definitely have. If you want to learn more about machine learning and deep learning and how to code them, there are some amazing notebooks here. So I got it from this one here, the multi-layer perceptrons. We come in this one. Oh no, that's for PyTorch. We come into TensorFlow. Now there's a function in here somewhere, very similar to the one we have. Boom, plot multiclass decision boundary. So there we go. So I'm going to copy this resource here. Number 2 is there. So I'll make sure to link those in the extra curriculum. But in the meantime, let's try and adapt our neural network to see if it works, even though we're working on classification right now. Because our neural network is plotting a straight line here, or predicting a straight line, I wonder if we can adapt it to a regression problem. Let's check that in the next video. In the last video, we created a function, plot decision boundary, to visually inspect our model's predictions, and we found that it's performing so poorly because it's predicting that the decision boundary is a straight line, whereas our data is circular. So we have a linear decision boundary, which linear is a fancy word for straight line, and we have non-linear data, which is another fancy way of saying non-straight data. Now, if we come back up here, I've just added a little tidbit in here in retrospect, but we've already discussed this. It's that, remember, wherever you see the key, it's an important point to note. Whenever your model is performing strangely, or there's something going on with your data you're not quite sure of, remember these 3 words: visualize, visualize, visualize. Inspect your data, inspect your model, inspect your model's predictions. And that's what we've done here. And we also discussed that since our model is predicting a straight line, might we be able to use it for a regression problem? Let's have a look. We'll write some code. Let's see if our model can be used for a regression problem. Now, we'll need some regression data. Now, I'm going to set the random seed here because we're going to create some regression data. And we'll make x regression so we don't override our already existing x variable. And I'm going to do tf range 0 to 1,000, and the step can be 5. And then y regression can be tf range 0 to, actually let's start from 100. So the function here we're trying to predict is just y equals x plus 10. That's the relationship between x and y here. Oh, sorry, plus 100, because y starts from 100, finishes at 1,100. X starts from 0 and finishes at 1,000. They both have the same step. So let's check this out. Remember, visualize, visualize, visualize. Inspect your data. Become one with the data. So there we go. Starting from 0, stepping up by 5, all the way up to 995. Starting from 100, stepping by 5, all the way up to 1,095. So we can remove those. Let's split our regression data into training and test sets. xreg train for x regression can be, let's just make it, how many values? We've got 1,000, so there's 200 total. And let's do the first 150, can be for the training data set. And the last the last 50 can be for the test data set. So xreg test equals x regression. We want just the last 150. So 150 onwards. That's how we can index that. Then we'll do the same thing for the y data. We could have actually done this for our circles data, but we'll move on from that one. We'll do that later on, I think. And then we go there. And now let's see. So we've got training and test data. Let's see if we can fit our model. Fit our model to the regression data. Wonderful. Model3.fit. Now before we do this, I want you to have a think. Will this work? Go back up, scroll back up in the notebook. I'm not going to give you any hints, but just step through each of the steps that we use to create Model 3. Build a model, compile a model, fit a model. We're doing step 3 right now, fit a model. Will this work or will it error? Inspect how we created it, inspect how we compiled it, think about the problem we're working on, regression, and have a think, will this work? I'll give you about 3 seconds or so to try that out. Well, I mean, you can pause the video, but 3 seconds for me. 3, 2, 1. All right, did you figure out why it will or won't work? You know what I hope you did? I hope you ran the code instead of scrolling back up. I hope you just tried it, because that's what I'm going to do. Oh no! What's happened here? Input 0 of layer sequential 2 is incompatible with the layer. Expected axis of -1 of input shape to have 2, but received input with shape none 1. So what's happened? We've got a shape issue, one of the most common issues in deep learning. So what's going on? We got train. Yeah, we've created our data sets correctly. Why hasn't our model worked? I wonder. So we've compiled our model for a binary classification problem. So we come back up here. Where's Model 3? Compile the model. We've set the loss function to be binary cross entropy. But what should it be if we're working on a regression problem? It should be something like MAE or MSE, mean squared error or mean absolute error. So let's go back. How about we write here, oh wait, we compiled our model for a binary classification problem. But we're now working on a regression problem. Let's change the model to suit our data. All right, so the only thing we're going to change in Model 3 is the loss function. What I might do is get rid of this code so it doesn't interfere with what we're going to write. So if you want to try yourself, all we're going to do is just recreate Model 3 exactly how it is. We're going to change the loss function. Instead of being binary cross entropy, we're going to change it to mean absolute error so that the loss function is regression specific. So give that a try, and otherwise I'm going to start writing it now. So we've got to set up the random seed so we get reproducible results. Set seed 42. Now, step 1, we're going to create the model. We'll just recreate Model 3. It's all right, we can override it. tf.Variable, and plus, what's the harm in having some more practice writing model code? tf.Variable. By the end of this course, I want you to have created over 100 models. Maybe even more, who knows? I'm not actually sure, I haven't counted. Maybe someone out there could count how many models we actually build together and then let me know, because that'd be pretty cool. You know what I should have done? I should have increased this number so we just knew the whole time what number model we were up to. Too late now. And so compile the model. Now this time with a regression specific loss function. Beautiful. Model 3.compile loss equals tf.Variable losses MAE, beautiful. And then the optimizer can be tf.Variable. We're going to keep the optimizer the same. We'll keep it as Atom. Optimizers.Atom. Remember, Atom is safe. Metrics equals, we need to adjust the metrics as well because it's a regression problem. We'll keep MAE there. And finally, 3 is fit the model. So we have model 3, we've recreated it, .fit on x reg train and y reg train, which is our regression data set. And we'll set it up for 100 epochs. Now you ready to run? 3, 2, 1. Ho-ho! There we go. Now what did it start with? Did we have... Oh, so the MAE is close to 250. And by the end, we go right down to 37. That's beautiful. So we see a reduction in loss and a reduction in MAE. But to make sure, seems like our model's learning something from these training metrics. Let's plot them. So just like we've plotted our circular data, we'll plot our regression data. So make predictions with our trained model. Y_reg_preds equals model3.predict x. Make it on the test data set. Oh, sorry, it's going to be, oh yeah, predict x reg test. Yeah, that's what we want. And now let's plot the model's predictions against our regression data. So we can create a plot here. We're not going to write as big and intricate a function as we did for our classification data, because this is regression data is just a straight line. And we're going to do a scatter plot. And on this scatter plot is going to be the training data. So x reg train, y reg train, and the color of the training can be blue. We'll label it training data so we know that it is the training data. Create another scatter plot, this time for the test data set. So test features and test labels. And we will color this with green and give it the label equals test data. And plot scatter x reg test. And now let's plot our reg predictions. And we're going to have to, no, I think that should be okay. We might have to, I wonder what dimension they are. Well, we'll check. If in doubt, run the code, wait for the error to pop up for us, and then we can see. And then plot legend. So that's what we've done. We've trained a regression model. We adapted model 3 to be suited for our regression data. We've made some predictions on the test data set. And now we're just plotting it, just like we did in the regression section. Training data, test data, predictions. Let's go. Figure. Oh, we want this to be fig size. Oh, would you look at that? Okay, so the predictions aren't perfect. I mean, if they were, the red line would line up perfectly with the green line, but they definitely look better than complete guessing. I mean, imagine if the predictions were all over the shop, like red dots everywhere. That would be basically guessing for this regression problem. Now, this means that our model must be learning something. However, it's still missing something for our classification problem. What's the difference here? What is the main difference between our data sets? I'll give you a hint. This regression problem is a straight line. Whereas if we come back, we discussed this before, our classification data is not a straight line. It's non-linear, but the decision boundary our model's trying to plot is linear, straight line. So, that might be the missing piece, the thing that we haven't introduced to our models yet. We haven't introduced non-linearity. And if you haven't heard of that before, that's okay, because we're going to discuss it in the next video. And probably maybe a couple of videos after that. So let's write that down. The missing piece. It's like we're on a treasure hunt here. Non-linearity. Alrighty, get excited, because we're going to learn one of the most important concepts in neural networks. Woohoo! I'll see you in the next video. Now, we've seen that our neural network that we've built can model straight lines with somewhat better than guessing accuracy. However, when it comes to non-straight lines, it's not doing too well. And so we also mentioned the missing piece. We're like treasure hunters here. The missing piece is non-linearity. So I cannot emphasize enough how important this concept is for neural networks. Now, before we write any code, I want to introduce to you a little question here. want something to think about just over the next few videos while we start to learn about nonlinearity. What could you draw if you had an unlimited amount of straight, in other words linear, and non-straight or non-linear lines? So just think about that. What kind of patterns could you draw? You have an unlimited amount of straight and non-straight lines. Let's look at our data again. We have some linear data. So you might think, is this possible to model with straight lines? I think so. And then we have some non-linear data. Not possible to model with straight lines. Now, you could post an argument to say, oh, well, Daniel, what if you just draw really small straight lines and go in between the gaps here? Well, that is one option, but let's just pretend that we need straight and non-straight lines to draw the patterns that we need. So keep thinking about this question. And again, before we write any code, we're going to have a little bit of a play around. I introduced the TensorFlow playground in a previous video. However, we haven't looked at it together. So I'm just going to playground.tensorflow.org and we can set up our data here. What I might do is zoom in nice and far. Okay, beautiful. So we have a few things going on here. We have data. Now this data looks very similar to our circulator that we're working with, except they're using orange and blue dots instead of red and blue dots. And we have some features, x1 and x2. We could pretend that this is our x0 and x1. Now, right now, this neural network has two hidden layers. What we might do is reduce this down to one hidden layer and one hidden neuron. So, a very simple neural network. And let's have a play around. What are these? We've seen the learning rate. All right. Let's switch this to, what have we seen before? I believe atoms is the default is 0.001. And activation, we haven't really played around with these. What we might do is switch this to linear. Now, we've seen what a linear data is, what linear data looks like. And we've got regularization rate, problem type, classification. All right, so let's just leave it at these settings for now. And I'm going to press play and see what happens. So we get the test loss. That starts to, it's just evening out at about 0.5. What does that remind us of? Do you remember our model that we built previously that only ended up with 50% accuracy? I think this is what's going on here. I know. To test this out, how about we recreate this neural network of what's going on? We've already got the data. We can create the hidden layer. And we can set the learning rate. We might see how we can set the activation too. All right, let's do that. Let's go back and let's write some code. So come in here. Now, how might we do this? Just as before. We're going to set the random seed and tf.Random.setSeed 42. And now let's go number 1. Create the model. Model 4. tf.Keras sequential. If we come down here, and then we want to go tf.Keras.layers.dense.1, and the activation can be, what did we set the activation to in here? Linear. How might we get access to that? Well, one shortcut is to just go linear as a string. Or we could do tf.Activations.linear. All right. Now we've got a parameter that we haven't seen before, activation, but we actually have seen this before. If we go back to our slides, and I think we might have to go a few back here. Yeah, there we go. We've got an activation parameter. Now we're going to start to look into, we've seen how we can add layers to try and improve our deep model. We've seen how we can increase the number of hidden units, but right now, these aren't really working for us. So we're up to changing the activation functions. All right, so we're working with this hyperparameter here. Now let's go back, and what we're going to do is compile our model because we want to recreate what we've done in the TensorFlow playground and see if we can replicate those results. This is a very good exercise to go through for yourself if you're playing around with the TensorFlow playground. To just recreate what you can see in there. Binary cross entropy. This is because we're working with a binary problem. Now, this is another way you can write the losses. You can actually write the losses in many different ways. We've seen this one, binary cross entropy, and we could even do it. Let me just introduce you to writing things as strings, cross entropy, just in case you see it like that somewhere else. And the optimizer, we can also set this to atom. That would be the same as writing it out like this, tf.Keras optimizers.atom. The benefit of being able to write it out like this is that we can set the learning rate. Remember, LR is short for learning rate. And the metrics can be accuracy. So if we've got the same thing so far, come back to our neural network playground. Features, X, we haven't passed our model data yet, but we have these. These are our blue and red dots. We've got one hidden layer with one neuron, and the activation is linear. The learning rate is 0.001. Okay. Now let's see if we can, number 3 is fit the model. And we're going to start to add the history variable here whenever we start to fit models now, because this will come up later on. Just want to start building that habit. All right. Let's do it. 100 epochs. I mean, this one's run for over 1,000, but we're just going to stick with 100 so we don't have an incredibly large output in our notebook. And shift and enter. All right, what kind of results are we getting? Wow. Looks like our model's performing worse than guessing right now. Is that aligned with the... Okay. So the TensorFlow playground is getting quite similar results. They're basically still guessing as well. If you were trying to separate these two, the blue and the orange dots, if you were just tossing a coin for 1,000 different times, and you got heads and tails 500 different times, well, you're going to get about these results. Now, let's remind ourselves of what our data looks like, because whenever our model's predictions aren't working very well, we can evaluate our model by looking at the evaluation metrics, or we can adhere to our model of visualize, visualize, visualize. So our data is 0. Get the 0th axis of X and the first axis of X, and we'll color it with Y, and we'll choose a color set up as plot.colorMap red, yellow, blue. So we're just reminding ourselves of what our data looks like. All right, wonderful. And now we've got model 4, which is a trained model, albeit looks like it's not performing very well. Let's check out its predictions anyway. Check the decision boundary for our latest model. So this is why we created a handy function before, our beautiful plot decision boundary function where we pass it our trained model. This can be model 4. We'll pass it our features, X and Y. What does it look like? Where's our model's decision boundary? Oh my goodness. It's all over the shop. So our model, if blue is the blue class and red is the red class, I mean, red's right up here. Yellow is the crossover because we've set our color map up as so. Our model is basically going, you know what, anything in this yellow could be blue or red, which is basically why our model's accuracy is below guessing. Now, what can we do? It looks like our model's still predicting straight lines. So what we might try is in the next video, or actually if you want to jump ahead, reset the TensorFlow playground and try playing around with activation here. What happens if you set it to a different value? See what happens, and we'll go through that in the next video. In the last video, we had to play around with the TensorFlow playground, and we saw that setting the activation function with one hidden neuron, one hidden layer, learning rate of 0.001, didn't result in a very good separation of the orange and blue dots, similar to the neural network that we built for our latest neural network that we built. So there's model 4. We just copied what we've got here. Now, I hope you've thought about this question here. What could you draw if you had an unlimited amount of straight, linear, and non-straight, non-linear lines? So remember, our data is that we're trying to model for classification is non-linear. So It's not possible to model with just straight lines alone. Now, if we come back here, we've spoken about non-linear. Right now our activation is linear. How about if we change this activation function to something that is not linear? So it could be any of these three values, even though we haven't seen what these are. Let's just change it to, let's try the top one, ReLU. Okay, and let's see what happens if we just run this. Still not getting a very good value. Wonder if we just keep it training for longer. Well, we're almost at 1,000 epochs now and it's still not improving. But before we explore different ones here, let's see how we might use the ReLU activation in our own neural network. So let's come back to our notebook. Let's just see if we can replicate. We'll take another practice and replicate this neural network here with TensorFlow code. So first of all, actually, we'll put in a note here. Let's try build our first neural network with a non-linear activation function. And now, when I say non-linear, I really mean just anything that is not linear. So we could choose linear, it didn't perform very well, but if we wanted to choose any of these which are not linear, we're going to start with ReLU, which is very common, as you'll see in your deep learning journey. So set random seed, tf random set seed 42. Now we're going to create a model, or we'll put number 1 here, so just remind ourselves, create a model with a non-linear, so just anything but linear activation. So we'll go model 5 equals tf.Keras sequential, and then we go back here, tf.Keras.layers.dense, and we'll just keep it the same as what we did before. We'll set activation equal to, you see here by default it's none. So this is where we're going to set it to non-linear. And we could do ReLU like this, or we could do tf.Keras.activations.ReLU. Wonderful. Now, 2 is we're going to compile the model just exactly as we did before. Model5.compile. Loss equals, what problem are we working on? tf.Keras losses. We're going to use binary cross entropy. And what optimizer have we been using? The atom optimizer. Optimizers.atom. We're just setting the LR to what we have in the TensorFlow playground. .001. Just the same there. And then the metrics is going to be accuracy. Now, number 3 is fit the model. Model 5. This is exciting. Our first model with a non-linear activation. Oh, we said we were going to start developing the habit of saving the history. X, Y, epochs equals 100. Let's see what happens. Oh, what did we mess up here? tf.Keras.optimizers, a typo, as usual. All right, wonderful. So we keep going. We're using a non-linear activation function. Remember, in this case, non-linear is just anything but linear. And again, our model ends up performing basically worse than guessing. So it's still not learning. What if we come back to our keynote? Now, we go back to the slide of where we looked at improving a model. So far, this is what we've tried. We've tried adding layers, we've tried increasing the number of hidden units, and we've tried changing the activation function as well as the optimization function. Far out, we've tried a fair few things. But we've only just tried changing the activation function. We haven't done that in conjunction with these two. So how about we try that? What if we increase the number of neurons and layers and change the activation function? I've got an idea. We can try that in TensorFlow Playground first. So, before the next video, go back to the TensorFlow Playground and try increasing the number of hidden layers, the number of neurons, keep the activation and the learning rate the same and everything else the same, but just increase the number of hidden layers to whatever you want. I think there's a maximum of 6. That's all right. Whatever you want, and increase the number of hidden neurons to whatever you want, and then run it and see what happens. And if you really wanted to, if your neural network works, or if it doesn't, reproduce it in TensorFlow code, and I'll see you in the next video where we're going to do everything we just talked about. Welcome back. How'd you go? Did you manage to get the TensorFlow playground to find the patterns or distinguish orange from blue dots? Did you get the test loss to decrease? The training loss to decrease? Did you increase the number of hidden layers or the number of hidden units? I hope you did, but if not, that's what we're going to go through in this video. Now, we've discussed that we've tried to improve our model, and we've tried adding layers, we've tried to increase the number of hidden units, we've even tried to add a non-linear activation function, because the data we're working with is non-linear. We've even tried changing the optimization function, but we haven't done all of these in conjunction with each other. So let's have a play around with the TensorFlow playground and see if we can adjust those parameters or hyperparameters, see if we can get this to distinguish patterns between orange and blue dots. So I'm going to add another hidden layer, and I'm going to increase this to, let's say, 4 neurons. Yeah, that's a good number, and I'll do the same for this layer. All right, I'm keeping everything the same. So I've just increased the hidden layer, increased the number of neurons. Learning rate the same, activation is the same. It's non-linear, so at the moment it's ReLU. And let's press play and see what happens. Oh, whoa, what do we got here? That's a good sign. The test loss is going down, and it's continuing to go down. Oh, wow. All right, we're nearly at 1,000 epochs. It's still going down. Let's just wait here for a second. Is it going to keep going down? Oh, look at this. So it's starting to be able to distinguish orange dots from blue dots. Now, once it hits 2,000, I think we'll stop there. You could leave yours running for longer and see what happens, but how cool is that? So just by increasing the number of hidden layers, adding a few more hidden neurons, and changing it to a non-linear activation function, we get much better results. Now, again, some great practice. Let's replicate this neural network in TensorFlow code. So we'll come back to our notebook, and time to replicate the multi-layer neural network from TensorFlow playground in code. And we'll set the random seed. So it's going to be tf.random.setSeed 42. And what did we have to do for our model? Well, we had 2 hidden layers with 4 hidden neurons each, and then we had an output, and we have a ReLU activation function, a learning rate of 0.001. All right, that seems pretty straightforward. So create the model. What number are we up to? I believe we're up to model 6 equals tf sequential. Beautiful. Now we need 2 hidden layers here. tf layers dense with how many hidden units? 4 or 6? 4. And then activation equals ReLU. Wonderful. We'll just come to the end of this. And then we'll create another one. tf layers dense. Oh, forgot the S there. 4 hidden units and activation equals ReLU. Wonderful. Now we'll go step 2, compile the model. Model 6.compile, just exactly the same as we've done before. Again, getting lots of practice here. Loss can be, we'll use the string notation for this model. Cross entropy, binary cross entropy that is. Optimizer equals tf.optimizers.atom, and the LR is 0.001, which is Atom's default learning rate. So we don't actually have to put that one there. And then finally, we're going to set the metrics. Metrics equals accuracy. And let's fit the model. So we're saving our results to the history variable. Model 6.fit on x, y, just the same number of epochs that we fit before. All right, well, let's see what happens here. All right, do we get any improvements? Oh, looks like our model's performing even worse than guessing. So below, what if we evaluate our model? Far out. What's the difference here? Evaluate the model. Model 6 dot evaluate, and we'll go X and Y. Why is our model performing far worse than what we, like this model trained, 2000 epochs. Maybe we need to train our model for longer. What if we did that? What if we come up here, make it 250 epochs? Let's try that. Oh, whoa, our metrics are jumping all over the place. So it definitely seems like our model is still basically guessing. What if we added, you know what I think it might be? You can't see it in this neural network playground, but I think it doesn't make sense the fact that we're dealing with features and we're dealing with a binary classification problem, and the last layer has 4 hidden neurons instead of instead of 1 for binary classification. So let's see what happens if we just add tf layers dense, because we want our output to be one or the other, right? Not 4 different options. We want it to be red dot or blue dot, not 4. So let's see what happens here. Accuracy, still 50%. Wow. Even after 200 or close to 250, it's about to be 250 epochs, we're still getting 50%. What if we evaluate that? What's going on? What should we do when we're not sure what our model is doing based on the evaluation metrics? We should visualize, visualize, visualize. So how do our model predictions look? So remember, we've got our handy plot decision boundary function. We're going to pass in model 6, X and Y. What type of decision boundary is our model creating? Oh my goodness. All right, so it's starting to realize that red might be towards the outside, but it's still operating with, it looks like straight lines. What gives? Our model looks like it's the exact one in the TensorFlow playground too. I mean, ideally, our yellow line would go inside or in between the red and blue circle. All right. Let's model this circle once and for all. We're going to build one more model, I promise, but actually we're going to build plenty more models throughout the course. But for this circle, I mean, we've done enough times. It's time to reveal the missing piece here. It is, if we come back to our keynote, we've looked at improving our model. We've altered the activation functions in the hidden layers, but we haven't changed the activation function in the output layer. So we've set up relu here. Now, what if we came back to our We looked at this right at the start. I mean, we could have come back to this to begin with, but I wanted to go through the concept of figuring things out. Let's go back to our architecture of a classification model. The typical architecture, that is. So if we have a look, what are we dealing with? We're dealing with binary classification. We've got hidden layers. Well, we've got 2 at the moment. We've got neurons per hidden layer, generally 10 to 100, but we've seen on TensorFlow Playground that 4 is enough for this type of data set. So we'll stick with that. Output layer shape is 1. We've set that up. Hidden activation is usually ReLU. Okay, we've set that one up. Output activation, sigmoid. So on our demo model here, we also have an activation on our output layer, but on the current neural network that we're working with, come back, model 6, we don't have any activation here. And remember, for a dense layer, the activation is by default none. So what should we do? If in doubt, we could refer to our little table that we have here, sigmoid, or we could search something like this. We could go, what activation function to use for binary classification? Now, maybe we go here. What activation function for the output layer? So regression, linear, softmax. Simple sigmoid works too, but softmax works better. Okay, we could dig through this information here. We could go back for another one. Here we go. The output layer contains a single neuron in order to make predictions. It uses, this is binary classification, that's what we're after, the sigmoid activation function. All right, That must be the missing piece that this TensorFlow playground doesn't show us. It doesn't show us the output layer, but that's all right. We've got TensorFlow code. So I want to issue you another challenge. If you want to model this circle once and for all, create a model like Model 6, but for the output layer, add in a sigmoid activation function. I'll let you do your research and give that a go, but otherwise, we're going to model this circle once and for all by introducing the output layer activation function in the next video. Welcome back. In the last video, we discussed that we're probably missing an activation function for our output layer. However, I hope you didn't take my word for it. I hope you tried to write the code yourself, but if not, let's do it. Let's model this circle once and for all. I'm getting sick of seeing these straight yellow lines. So let's set the random seed. As usual, you can probably tell that my coding hands are eager to write this neural network and get this circle modeled. So let's do step 1, create a model, just as we have before. I believe we're up to model 7. Fingers crossed, this is lucky model 7, you know. And we're going to go sequential. Go there. TF Keras layers. Just going to be the exact same hidden layers as what we've been using before. The activation equals ReLU. Wonderful. Come back. TF Keras layers dense. 4 as well. Activation equals ReLU. TF Keras dot layers dot dense. We want 1 for the output layer because we're dealing with binary classification, one thing or another. And here is where we're going to introduce the magical. We could do TF Keras activations dot sigmoid, or if we wanted to keep in line with the string notation that we've been using, we could just turn this into sigmoid. Now again, where does this come from? We could ask Google, or we could check out the typical architecture of a classification model. So binary classification, hidden activation, usually ReLU, or the output activation is sigmoid for binary. When we deal with multiclass, we'll have to deal with softmax, so keep that in mind going forward. Now we'll come back. All right, our model architecture is looking great. Let's compile it. Compile the model. Model 7.compile. Now we want to go loss equals TF Keras losses dot. No, we were using string notation. Come on, Daniel. Let's go binary cross entropy. Wonderful. And then optimizer can be TF Keras optimizers atom. We'll set the learning rate to be 0.01. Again, that's the default. We don't necessarily need to do that, but just keeping in line with staying true to our TensorFlow playground setup. And we will go metrics equals accuracy. Wonderful. Now, let's fit the model. Ooh, I'm eagerly awaiting to see if the results for this one are better than our previous model. This is the fun part of neural networks and deep learning, is running so many different modeling experiments. Epochs equals 1. Oh, let's watch the training. I was about to set verbose equal to 0, but let's watch it. If this neural network's going to work, I want to see those metrics going where they should go. Accuracy, it starts. Are we going up? Yes. Oh my gosh. Look at that. Look at that. We finished with an accuracy before we added that output activation function. We were getting about a 50% accuracy, and now we're borderline 99%. But again, let's not trust just the metrics. Let's try number 4 is evaluate our model. So model lucky number 7, that's where we're at. Evaluate X and Y. Are we getting the same? Wow, we are. Loss below 0.3 and accuracy is 99%. How does that line up with our TensorFlow playground? So that loss is getting almost 10 times lower, but this is fit for 2,000 epochs. Maybe ours would somewhat approach that if we kept training. But again, let's not just trust the metrics. Let's visualize. Let's visualize our incredible metrics. So again, we created this beautiful function a few videos ago because we want to use it multiple times. Plot decision boundary. Model number 7, X, Y. Are you ready? 3, 2, 1. Oh my goodness. How much better is that? So it looks like our model has basically perfectly found the decision boundary between the red and blue dots, except for maybe a couple of points. Oh, that one got caught, and that one got caught there. So that's why we're not getting a perfect result, but we're very close. That's 99% accuracy between two evenly spread classes or two evenly spread labels. That's pretty darn good. But I have a question for you. I want to put this down here. And we've discussed this previously, but I'm going to put the question emoji. It's a little challenge. So question equals, or equals, I'm too used to saying equals. What's wrong with the predictions we've made? Are we really evaluating? So if we're looking at this, our evaluation metric and our plotting of predictions, are we really evaluating our model correctly? Here's a little hint. What data did the model learn on? And what data did we predict on? Now have a think about that. You probably know the answer already. If not, perfectly fine. But before we answer that, I want to emphasize what we've just covered, which is back to the question we had before. If we go to our non-linearity slide, I posed this question a couple of videos ago. What could you draw if you had an unlimited amount of straight, linear, and non-straight, non-linear lines? And then we looked at our linear data, and we looked at our non-linear data. So the combination of linear, straight lines, and non-straight lines, if we go back here, so non-linear functions, remember we haven't even discussed what ReLU is or what sigmoid is, we just know that it's not linear. So we come back, linear, and these three are not linear. That's all we've discussed for now. But this is I'm going to even write this down. So let me put a key here. If you want to take away anything from the few videos we've just gone through, is that the combination of linear, which is straight lines, and non-linear, which is non-straight lines, that's all you need to know for now, functions, is one of the key fundamentals of neural networks. And notice key is on purpose because I've got key there. Now, back to our question. Just think of it like this. If I gave you an unlimited amount of straight lines and non-straight or non-linear lines, you could essentially draw any pattern that you wanted to. Now, that is essentially what our neural networks are doing. This data set is relatively easy, but if you imagine if we're working on a whole bunch of different other data sets, such as building a neural network to understand what's in a picture, there's almost an unlimited amount of things. Look up if we go food, images. If we wanted to build a neural network to identify different patterns in pictures of food, look how many different patterns there are here. We need a whole bunch of non-straight and straight lines. So that's the essence of what a neural network is doing when it looks at different examples of data. It's drawing patterns with straight and non-straight lines through it. So if this doesn't really make sense for now, you might even be thinking, hey Daniel, I've never actually seen a linear function or a non-linear function before. Well, you kind of have. We've been using the whole time. They're what power the layers we've just built. So with that being said, in the next video, let's take a look at applying these linear and non-linear functions that we've been using in our neural networks, but just applying them on their own. So I'll see you there. In the previous video, we modeled our non-linear classification data once and for all. I mean, look at that. That's a beautiful sight, isn't it? Our decision boundary is basically splitting them perfectly. Now, we've also discussed the concept of linear, or straight lines, and non-linear, non-straight lines, or functions. But we haven't really built up an intuition about them. We've just got familiar with the names of some of them. We've looked at ReLU, and we've looked at sigmoid. But let's start to build up an intuition of them. So right here, now we've discussed the concept of linear and non-linear functions, or lines. Let's see them in action. So to do so, how about we create a toy tensor, which is very similar to the data we pass into our models. Because we're dealing with TensorFlow, all of the data we use gets encoded into a tensor. We pass that tensor to a neural network. It figures out patterns and outputs another tensor. So let's go A equals tf.Cast. I'm going to go tf range. I want just a tensor, a nice one from -10 to +10. And I want it to be of float 32. Let's have a look. Okay, nice and simple. Just -10 all the way up to 9 because it includes 0. But it's 20 long. Now let's have a look at what it looks like. Visualize our toy tensor. plt.plot A. Wonderful. Nice and straight line. What would that be called? What's a straight line? It's a linear line, right? Now, what activation function did we just try in our output layer? The sigmoid. Okay, so how might we apply this sigmoid activation function directly to tensor A? I've got an idea. Why don't we look that up? TensorFlow sigmoid activation function. tf.Keras activation sigmoid. Okay, wonderful. Oh, the sigmoid activation function. Sigmoid x equals 1 divided by 1 plus exponent to -x. Okay, what if we just did sigmoid activation function? What does that look like? We're going to get some fancy math notation, I'm guessing. Yeah, there we go. Okay, so sigmoid z equals 1 on 1 plus e to the power of -z. And we get a line like that. Oh, so see how that's non-linear? All right, enough looking at pictures. Let's try to replicate this. We could do it tf.Keras activation sigmoid, but how about we start off by just replicating this? So what I would do in a case scenario like this where I'm trying to replicate something, I would go, let's start by replicating sigmoid. And I'd put this here. So I'm trying to build a function that replicates this here. I was just trying to point at the screen, but I realized you can't see that. So let's go def sigmoid, and it's going to take an input x. And then how about it's only this, 1 divided by 1 plus. Now, to get the exponent, let's look that up. Can we do it in TensorFlow? TensorFlow exponent. tf math exp. Wonderful. Does it have an alias? Oh, tf exp. All right, exp. So if we go tf.exp, pass in -x. Is that our sigmoid function? Really? That's all it is? So let's try it out. Use the sigmoid function on our toy tensor. So we created A up here before. Remember, this is what A looks like right now. It's linear. Now if we use our sigmoid on A, all right, we get a whole bunch of what looks like gibberish numbers, but let's plot them. That's a much better way to look at them. How do we do that? Plot our toy tensor transformed by sigmoid. So plt.plot, we want to go sigmoid A. What do you think this will look like? Give you a second to think about it. Let's check. Ho-ho! That's what's up! Now notice here that the values are between 0 and 1. That might be something we look at later on, but the most important point here is that this line was originally straight and has now been modified to be non-straight. Now, where is the intuition there? If we come back, remember how we couldn't draw a curved line around our data? But as soon as we added this sigmoid activation function to our neural network, it was like, now that we've seen what it does to a straight line, it was like we gave our neural network a tool to go, hey, you've been trying to draw patterns with just straight lines before, but now you've got this non-straight line, so use that as best you can to find better patterns. And as it turns out, it was able to find better patterns. So let's not stop there. Let's keep going. What was the other activation function that we've used so far? We'll come up here. We've used ReLU activation. All right, so let's see. How can we replicate this? Because that looks pretty cool. I wonder if we can do the same for ReLU. Let's go another tab, TensorFlow ReLU function. And what do we get? tf.Variable activations ReLU. All right. Well, it looks like we can do very similar notation to our sigmoid function. But does it have a definition of what ReLU is? Oh, it's just the max between x and 0. Oh. So does that mean it's going to make all negative numbers 0? Or we could even just go, what does ReLU do? In a neural network, the activation function is responsible for transforming the summed weighted input from the node into the activation of the node or the output for that input. We could dive into that. ReLU is the max function x0. What if we go images? Is there a function of it? Equals 0 for x less than 0, or x for x equal or greater than 0. Okay. Why don't we just replicate that? Max, 0, or z. Okay. Let's give that a go. Let's recreate the ReLU function and see what happens. Oh, and one thing before we do, notice what this line looks like. How does it look compared to our original tensor? Our toy tensor that we created above. So maybe we go def ReLU. And we want to return. How do we get the maximum in TensorFlow? We can just do max. Is it maximum or just max? Maximum. Wonderful. We want to return the maximum between 0 and x. That's all we've done for ReLU. If we come here, we want to go all. Is there a Wikipedia page? Wikipedia is usually pretty good. There we go. Rectify on neural network. This is all we've written. ReLU equals max 0x. That's it. That's all we've done. Okay. Now let's pass our toy tensor to our custom ReLU function. ReLU A. And what's going to happen? What do you think is going to happen? Well, let's check it out. All right. How is this different to our original tensor? Just by looking at it, this one's a bit easier to look at than the sigmoid. But see how these are all 0? It seems like ReLU, all it's done is it's turned the negative numbers to 0. And that we've done that with the maximum function by just going, hey, look at the input you're getting and give me the maximum of 0 or the number itself. So is 0 larger than -1? Yes, it is. So we set it to 0. All right. Now, better still, let's see how this looks. So plot ReLU modified tensor. I'm going to go here, plot ReLU A. And let's see. Ha ha! Now what is that? We come back, or let's just bring our straight line tensor down here. So it started out straight, and now this is, you could still argue that this is straight, but it's got a kink in it. So now we have a bunch of tools. We've given our neural network, hey, here's this curvy line, and here's this bendy line. Now, you've got these two tools. Let's start drawing patterns in our data. I mean, I could draw some pretty cool shapes if I had this curvy line and this bendy line. Now, let's not stop there. We've got one more activation function that we've tried. Remember in our neural network playground, the first thing we tried was linear, and then we tried nonlinear. So let's do that. Let's for completeness, let's see how. Let's try the linear activation function. So might just do what we did before, TensorFlow linear activation function. tf.Variable activations linear. linear activation function, pass through. What does it do? Arguments x, the input tensor, returns the input unmodified. Are you serious? We just put a tensor into the linear activation function and it just returns the same tensor. Did that even need a function? Oh, well, we said we're working for completeness. We might as well try it out. We'll go tf activation.linear. It's not even fun to replicate this one. Has no model activation. Oh, activations. That's what we need. We need the S. Come in here, shift and enter. Wow, are you serious? That's all that does? Just our exact same tensor? Well, for completeness, let's does the linear activation function change anything? So plot tf activation.linear. A. We'll see. Oh, again, I'm making the same error. Hold on. This can't be real life. Let's go. Does A even change? A equals tf.activations.linear. All of the elements are still the same. I guess, well, the linear activation function lives up to its documentation, returns the input unmodified. But this is a fundamental concept of what we've just covered. Now, let's come back to our slide. I've just prettified all the code we've just written, but the important thing is that we've written this code and we've seen it happen. But it makes sense that the model didn't really learn anything using only linear activation functions, because the linear activation function doesn't even change our input data in any way. So it's just basically passing the same input data through the entire neural network, and the outputs, no wonder they're basically as good as guessing, because it hasn't changed a single thing. Whereas with our nonlinear functions, such as sigmoid for the output layer, we give our neural network this tool here of using this curved line. And the same thing here for the ReLU function. When we give our model nonlinear functions, it's able to deduce patterns in nonlinear data. Whew, that's a fairly important concept. Now, we've only covered 2 activation functions here, but the premise of what we've just seen is the concept of nonlinearity is we've covered that. So that's the main takeaway you need to take away from this series of videos, is that neural networks use a combination of linear activations and nonlinear activations to find patterns in data. Now, if you want a resource for learning more about activation functions, there's the machine learning cheat sheet, activation functions. I'll leave this in the resources section, but mlcheatsheet.readthedocs.io actually has a whole bunch of different stuff. But here are some of the most popular and useful activation functions. We've seen linear, ReLU, leaky ReLU is a different form of ReLU, and sigmoid. I'll let you go through here. Maybe some of your extra curriculum could be to reproduce these in TensorFlow code. However, we're going to push on, and in the next video, we're going to see how we can evaluate and improve our classification model, this one that we've built here. So, with that being said, I'll see you in the next video. In the last few videos, we tackled the important concept of nonlinearity, and we learned that the combination of linear straight lines and nonlinear non-straight lines functions is one of the key fundamentals of neural networks, or in other words, how they find patterns in data. And we even saw a few different examples of linear functions. We even rebuilt our own nonlinear functions in the sigmoid activation function and the ReLU activation function. But now it's time to evaluating and improving our classification model. Alrighty. So do you recall that in a previous video I posed the question of what's wrong with the predictions that we've made so far? If we scroll back up, again, jumping all over the place here, but I did pose a question before. What's wrong with the predictions we've made? Are we really evaluating our model correctly? Hint, what data did the model learn on, and what data did we predict on? So far, in our toy example, we've been training and evaluating, or training and making predictions on the same data set, but why is that wrong? We'll come down here. What should we do? What type of data or what data set should our model learn on, and what data set should we evaluate our model on? Now, if you answered that question with, we should train our models on the training data set and test our models on the test data set, you'd be 100% correct. But at the moment, we don't have a training or a test data set. So let's remind ourselves of the 3 data sets, possibly the most important concept in machine learning. And I know I say that about a lot of the concepts we've talked about, but this is probably the number one thing to do with data. So we've got the course materials, as if you were studying at a university course, is the training set. The validation set is the practice exam, and the test set, the test data set, is the final exam. And the goal here is for our machine learning model or deep learning model to generalize. In other words, the ability for our model to perform well on data it hasn't seen before. So, what do you think we should do to properly set up our machine learning model training and testing? Well, if you guessed, we should create... Actually, let's write ourselves a little note here. So far, we've been training and testing on the same data set. However, in machine learning, this is basically a sin. So let's create a training and test set. All right. So how many examples do we have? Let's check how many examples we have. We can get length of x, that'll tell us. Beautiful, it's 1,000 because we use the make circles function all those videos ago to create our data. Now we could, because our data is in random order, right, if we look at that and we look at y, we could randomly split this using scikit-learn's train test split. This one here. Or we could create a train and test data set by indexing. I'll let you choose how you do yours, but I'm going to create mine using indexing. So split into train and test sets, and then I'm going to go here. I'm going to set x train and y train equal to, we're going to do an 80-20 split. So 80% of this of our samples is going to be training data, and 20% is going to be testing data. So the first 100 samples will be, or 800, sorry, of x and y will be training samples. And then we'll do the same for x test and y test. However, these will be the last 200 samples. So from index 800 onwards. Wonderful. Now let's check the shape of x train and x test, and then y train shape and y test shape. What have we got at the output? Okay, x train and x test. So there's 800 examples in x train, and it's of a shape 2. That's excellent. And 200 examples in x test. And then y train has 800 labels, and then y test has 200 labels. Beautiful. So now we've got a training and test set. How about we recreate a model, fit on the training data, and then we can evaluate it on the testing data. This one here. So let's write that there. Let's recreate a model to fit on the training data and evaluate on the testing data. How we should have been doing things right from the start. So first of all, we'll set the random seed. tf random set seed 42. And then we'll go number 1 is create the model. Now, again, we're retyping the same code because we're making the same model as Lucky Model 7, but we're getting ourselves, or we're getting a lot of practice writing TensorFlow model code, which is very important because we are doing a TensorFlow deep learning course. So if we go over here, and what was it? tf.Keras, well, we could find model 7.summary. What's this going to tell us? Okay, so we had 2 hidden layers with 4 hidden neurons each. So let's recreate that. Layers dense 4. And what was our activation function? It was nonlinear. Relu. Come back here. Then we'll create another layer, tf.Keras layers. Dense 4. Activation equals relu. And then, what was our output activation? We recreated it again. If you need to, refer to the slide which has the activation for the output layer of a binary classification model. But it was sigmoid. So now, let's compile the model. So we want model8.compile. We want to set the loss function to binary cross entropy because we're working with a binary problem. And then we want to set the optimizer equal to tf.Keras optimizers.atom. However, we're going to make a change here. We're going to change the learning rate. So Atom's default learning rate is 0.001, but I have a feeling that if we increase it to 0.01, our model might be able to discover the patterns it found in our data faster than what it did previously. So with model 7, we fit for 100 epochs. If we come back up here, we fit for 100 epochs. But it looks like our model was a little bit slow out of the gates. So it really didn't start learning much. So it's still in the 50s here. And then it's not until about halfway that it starts to really increase up past the 60s in about 5 epochs. And then the 70s in about another 10 or so epochs. And then it gets really close to 100% accuracy. So the reason why, do you remember how we discussed what the learning rate is? It's okay if you don't, but we mentioned it briefly in a previous video. I'll set the metrics here, but the learning rate dictates, because let's take a step back. The optimizer tells our model how it should improve or how it should update its internal patterns that it's learned. The loss function says how wrong those patterns are, and then the optimizer says, hey, you should improve them in this way. And the learning rate is how much our model should improve those patterns. So if we set the learning rate to be a lower value, say Atom's default, such as 0.001, this might be the equivalent of saying, hey, every time you take an epoch, improve your weights by 0.001. So if we were to change it to 0.01, we've increased it by 10%. So basically every epoch, we've given our model the potential to improve its weights by 10 times as much. Now that's not exactly how it works, but that's how I intuitively understand the learning rate. And in practice, you'd be surprised how much that simple definition of going, hey, the higher the learning rate, the more our model will update, works in practice. And by the way, Atom's default learning rate of 0.001 and these other default parameters here are actually very good for the majority of problems that you'll work on. Of course, as you start to get more and more into the deep learning world, you can start to tune these to your problems, but you'll find that a lot of the values that we use in TensorFlow, all of these parameters that are hard-coded already, have been experimentally found as very, very, very good. So now let's go here. We're going to fit the model. Model8.fit. We're going to fit on the training data. Oh, what have we been getting into the habit of the last few videos? That's right, setting the history variable. Ytrain epochs 25. So I've increased the learning rate by 10, but decreased the amount of epochs our model is going to look at, or in other words, the amount of times the model is going to go through the training data by 4 times. So let's see if it can still get just as good results with only 25 steps versus 100 steps. What have we done wrong here? Oh, we need to set this as model 8. All right, where do we get to? Oh, do you notice what's happened here straight away? So we have epoch 1 out of 25. We start at 54%. And then we're into the 70s after only 8 epochs. And then we're into the 90s after only 15. I mean, if we go back up to our previous model, we didn't reach the 90s until epoch 77. Wow. Okay. So if we come down here, look at that. By the end, we're borderline 98% accuracy after only 25 epochs. Now, the real test here, of course, is for evaluate the model on the test data set. So let's go model 8 dot evaluate. Now that we have a test data set, x test, y test, how does it perform? Wow. So on the test data set, in other words, data our model has never seen before, it gets an accuracy value of 100%. That means every single test value, it got correct. Out of 200, it predicted them all correct. That is amazing. Now we can really evaluate this. How can we do so? By plotting the decision boundaries. We've done this for our complete data set before, but now let's do it both for the training data set and the testing data set. Plot the decision boundaries for the training and test sets. Plot.figure, fig size equals 12, 6, beautiful. Plot.subplot, 1, 2, 1. Plot.title, let's go train data. So here we're just saying, well, hey, we want to create a subplot. We want it to have, I believe it's rows, columns. So we want it to have 1 row, 2 columns, and the first value is going to be the training plot. Plot decision boundary. And then we're going to pass it model 8, our trained model. X is going to be X train, our training data. And then Y is going to be Y train, our training labels. And then we'll set up the second subplot. This is going to be 1, 2, and the second plot. So 1 row, 2 columns. The first one is training. The second one is going to be test. And then again, plot decision boundary. Model 8. X equals the test data set. So X underscore test. Y equals the test labels. Beautiful. And let's show our plot. Doing binary classification. Oh, would you look at that? So our model's decision boundary, the yellow line, goes through the training data. It misses a few examples here. I think it might have missed that one, the red dot, and I think this blue dot. So that's why our model doesn't get 100% results on the training data set, but that's okay. We want our model to generalize to data it hasn't seen before. So when we look at the test data set, it gets about 100%, or it does get 100%, not about 100%. It gets 100% accuracy. Excellent. And that was after 25 epochs. So the main takeaway is that all we did was we took our model 7, the model that was working, but we increased the learning rate by 10 times. Now, again, this is one of those hyperparameter things that won't always work. Our Atom's default learning rate is actually very good for the majority of problems you're working on. The only reason I set this to be a little bit higher is because I had an inkling that our model might learn a bit faster because it performs so well on our data set. So again, in practice, you may take a little bit of tweaking for the learning rate, but we'll see in an upcoming video how we can design a function to find the ideal learning rate value for us. But in the meantime, let's since we've been saving our model's training history to this history variable, in the next video, let's see how we might visualize that training history. You may have noticed in a few of the previous videos, and whenever we called the fit function and created our different models, we've been getting into the habit of setting history equals model8.fit something, or model whatever number.fit. Now, I think we have seen this before, plotting the history variable, but we haven't discussed it very recently. So let's go through that now. Let's see how we can plot the loss, or also referred to as training, but probably most often referred to as loss curves. And let's go here. Now, the reason why we're doing this, if we come back to our keynote, let's find where's our Data Explorer's motto? First of all, what is our Machine Learning Explorer's motto? It is visualize, visualize, visualize. And we've had a little bit of experience visualizing our data and our models and our predictions, but not so much training. So that's what we're going to cover here. And of course, it's a good idea to visualize these as often as possible. So let's see what the history variable is. But first, to understand it, how about we look up the docstring of TensorFlow fit function. What does this give us? Here we go, tf.Model. So this is the model class, which our sequential model is built off. And then when we call fit off this, so if we look for fit, does it have here? Once the model is created, you can config the model with losses and metrics with model.compile. We've seen that in practice. Train the model with model.fit. That's not what we want. We want the fit function. We want the fit function to discuss what it returns. Here we go, fit. So we can actually pass a fair few things to fit. If we look here, if we go X, Y, batch size, a whole bunch of things. We'll see a fair few of these throughout the course, but if you want to skip ahead and read them, you definitely can. But I want to see what it returns. Where do we go here? Returns. Here we go. A history object. History.history attribute is a record of training loss values and metric values at successive epochs, as well as the validation loss values and validation metrics if applicable. Beautiful. So that's why we've been setting up this history variable. Now, history, the documentation just said that history.history. So what happens if we go history.history? What does that give us? Accuracy. Okay. So it looks like there's about 25 values there. So I think it tracks at every epoch, which is beautiful. So really what history tracks for us is this output here. And it's good to look at these in numerical form, but we can also look at them in visual form. So let's convert the history object into a data frame, make it nice and tabular so we can structure it up. pd.dataframe, and we want to go history.history. Let's see what it looks like. Beautiful. So we can see our model's loss started at around 0.7 and decreased right down to about 0.14. And the accuracy started at about half, 50%, and then increased right up to 97%. And that was on the training data set. So now, how about we look at the loss curves? We just plot this. So plot the loss curves, pd data frame history.history, and then we're going to just go simple plot. I believe by default it's going to be a line plot. So this is going to be model 8 training curves, or we'll call them loss curves because that's what we've been calling them, loss curves. And let's have a look. Wonderful. Now that is probably the ideal loss curve scenario we want to see for a binary classification problem, or actually most classification problems, because accuracy metric is going up and loss is going down. So actually for many problems, I think this is a key we can add in here. I'll write in here, note the loss function, because remember, what is the loss function? It's how wrong our model is. So for many problems, the loss function going down means the model is improving. The predictions it's making are getting closer to the ground truth labels. Now you might be wondering, okay, I understand that. It's good to see the loss curve going down, but what other values or what other value can I generate from looking at plots like this? Well, in future videos, we're going to see how we can compare multiple different models and check out their loss curves. So the value in this is if we were running, say we ran 10 experiments at the same time, and we plotted all of our models' loss curves together, and say model 8 had a learning rate of 0.01, model 10 had a learning rate of 0.001, and we noticed model 8's loss decreases far quicker than model 10's, but after about 100 epochs, model 10 starts to catch up. So that's where we'd sort of be able to use this visual knowledge to guide our future experiments. So just keep in mind that whenever we set the history variable, we can inspect our model's training curves by plotting them like this. And we'll see in the future another way to do this with TensorBoard. But for now, let's just leave it there. And in the next video, we're going to check out how we can use loss curves to find the best learning rate. So I'll see you there. In the previous lectures, we've seen how much the learning rate hyperparameter can influence our model's training. So wouldn't it be great if we had a method that we could use to find the ideal learning rate? I mean, a value which, when our model started training, meant that its loss decreased as fast as possible. Because remember, the loss is a measurement of how wrong our model is. So if we want to decrease the loss as much as possible, what value could we set the learning rate to be? Well, to do this, we're going to have to visualize our loss decreasing and potentially decrease our learning rate during training. Now, have we visualized the loss decreasing? I think we have. There we go. Okay, so we've visualized the loss decreasing. Now, how might we decrease the learning rate during training? Because so far we've only hard set the learning rate, so using something like LR equals 0.01. But I haven't actually introduced you the answer to this question that I just asked, so don't worry if you're not sure. But that's what we're going to do in this video. It's finding the best learning rate. And to do so, I'm going to introduce a new concept which is called to find the ideal learning rate. In other words, it's the learning rate where the loss decreases the most during training, because remember, that's the loss metric. We want that to decrease during training. We're going to use the following steps. So the first one is a learning rate callback. Now, callback is the new concept that we're going to talk through this lecture, or we're going to code it out actually. Now, a callback, if you're wondering what it is you can think of a callback as an extra piece of functionality you can add to your model while it's training. So when our model trained before, it went through the data and found patterns, but it'd be great if we could execute some other kind of functionality while this training has taken place. That is where callback comes into play. So that's the first one, a learning rate callback. We'll see that in a second. And we're going to need another model. So we could use the same one as above, but we're practicing building models here. And finally, we're going to need a modified loss curves plot. So very similar to what we've got here, this loss curve, but we're going to have to modify it because what we're going to set up is a learning rate callback to start at a certain value of a learning rate and gradually decrease or increase that learning rate during training. And then we'll make another plot to plot the loss versus the learning rate to find out the learning rate value that the loss decreases the most. Now, if that didn't make sense, remember, what's our motto? If in doubt, code it out. So let's get started. We're going to create a new model. So set random seed, tf random set seed, beautiful. Now we're going to create a model. Now it's just going to be the same as model 8. Remember how I said we're going to have heaps of practice coding up models? Well, we're almost up to 10 models so far in this one little section. So model 9 equals tf caras sequential. And that's really the only way to get better at programming or any kind of machine learning or data science is to just to keep writing more code. Keep working on different things. There's no secret here. Relu, we could go up and see what it is, or you could just follow along with what we're doing. So looks like it's got, we forgot the layers. It's got 2 dense layers with 4 hidden units with the Relu nonlinear activation. Beautiful. And then we have an output layer with 1 hidden unit, and we're using the sigmoid activation. Beautiful. So now what's next after we create the model? So we're going to compile the model, just the same as before, except now we're using model 9. Model 9.compile. Loss, we're working with binary. So we're going to do binary cross entropy, and then we're going to put in here the optimizer. Let's use Atom. We use the text-based version of Atom. Metrics equals accuracy. Beautiful. And now, here's the step that's going to be different. So we're familiar with these steps here, but we're going to introduce, as I said, a learning rate callback. There are many different types of callbacks, but for this one, we're using a learning rate callback. And so a callback works during model training. So to get it to run during model training, it has to exist before model training. So before we call model 9.fit, our callback has to exist. So let's create that. Create a learning rate callback. So we're going to call it LR scheduler, because as you'll see in a second, if we go tf keras callbacks, there's a callback called learning rate scheduler. Beautiful. And now how do we find out the doc string of this? We can press Command-Shift-Enter, or Command-Shift-Space, sorry. It came up automatically. So this is learning rate scheduler. At the beginning of every epoch, this callback gets the updated learning rate value from schedule. So schedule is this parameter here, function provided at init, with the current epoch and current learning rate, and applies the updated learning rate on the optimizer. Okay, so this is kind of a way of saying every epoch, if we put in some functionality here to change the learning rate, it's going to, this callback, if it's running during the fit function, it's going to give our optimizer, in our case Atom, the updated learning rate. So let's see what we might do. What we're going to do is do lambda epoch. Oh, lambda needs a B. Epoch, and then we're going to go 1e -4. So this is just 10 to the power of -4 here, and then times 10 epoch divided by 20. Wonderful. So essentially what this is saying is for the learning rate scheduler, every epoch to traverse a set of learning rate values starting from 1e -4 and increasing by 10 to the power of the epoch divided by 20 every epoch. So let's see what that looks like. Now we go here, fit the model. So this time we're going to pass LR scheduler callback model. Oh, we're getting into the habit of saving history. History 9 equals model 9.fit. Now let's pass it our training data and training labels. Epochs, we'll run it for 100 epochs, and then callbacks. Now callbacks come as a list, so we're going to pass it in LR scheduler, because you can pass multiple callbacks here. So say you want to callback 2, callback 3. I'm not sure why I'm putting an underscore between call and back. It's actually just one word, but that's all right. We don't have callbacks 2 and 3. We only have 1. So let's just see what's going on here. We run this. Beautiful. Now our training appears to be just working as normal. We're very familiar with this. We've seen this before. But I want you to have a think about it. What might be different now? If we passed it our learning rate scheduler here, what's it going to do every epoch? It's okay if you're not sure, because remember our motto, if in doubt, code it out. Now, what we can do is check out the history. Remember we saved it to history 9, so we'll turn it into a data frame so that we can plot it. History 9.history, and then we're going to go plot fig size, only my favorite two numbers in poker, 10.7. Also just a handy size to put out in this kind of window. X label equals epochs. Beautiful. Let's see what this looks like. Oh, okay. So this looks a little bit different to the loss curves that we plotted before. It's the exact same sort of plot that we created up here. So this is our model 8 loss curves. So see here, history.history. Now this is model 9, history 9.history plot. We've just given the X label epochs. So if we look at this axis, the y-axis, our learning rate starts very low, basically 0. And then as the epochs go on and on and on, it starts to increase. Okay, so that's essentially what this code up here is doing. So it starts at a low number, 1e, -4, and every epoch it increases by 10 to the power of epoch divided by 20. So that's why towards the end we get this exponential curve. It starts to increase really fast. But what happens here with our accuracy? Our accuracy seems to go up slightly but then goes down, and the loss goes down fairly significantly here, and then it stays low but then goes back up. So looking at this, what did we want? What did we want before? We wanted the learning rate where our model's loss decreases the fastest. So potentially this value here, whatever it is, the learning rate at let's say 45 epochs maybe, this is where our loss seems to be decreasing the fastest. I got an idea. Let's plot the learning rate values during training versus the loss. So how might we do that? Let's go plot, because we can't really see what's going on here. Let's get accuracy out of there and let's just compare learning rate to loss. So plot the learning rate versus the loss. So our LRs is, what did it start at? It started at 1e -4 times 10 to the power of, now we're going to have to do, we need a range. So tf range 100, because that was how many epochs we did divided by 20. How does that look? That should give us, there we go, shape 100, beautiful. So if we go len LRs, LRs is short for learning rate, there we go. We have 100 different values of learning rate. So see how it starts here at 1e -4, and then it slowly increases as we go along. All we've done with this line of code here is we've just replicated the same thing we passed to the learning rate scheduler, except that we had to substitute in 100 as an integer for epoch because we set 100 here. That's all we've done. So these are our different learning rates that our model tried out. Now what can we do? How about we create a plot, plt.figure, fig size equals 10, 7. Wonderful. Now we're going to do a semi-log x plot. So that means, this just means we want log on the x scale. Make a plot with log scaling on the x-axis. You'll see what I mean by that in a second. So log x, LRs, so we're just passing it this that we created, which is just a tensor of this shape. May have to be NumPy. I'm not entirely sure. We'll find out. If in doubt, run the code. And now we're going to go history. We're going to get the loss. So this is what we want. So on the x-axis, we want LRs, and on the y-axis, we want the loss values from our model history. Beautiful. Now we're just going to decorate our plot with x label can be learning rate, and the y label can be loss. And finally, let's give it a title, plot.title, learning rate versus loss. Beautiful. What does this look like? Aha. Okay. Now, before we even discuss this, I want you to maybe pause the video for like 10 seconds and just have a look at it and have a think about, where do you think our ideal learning rate would be? Totally okay if you're not sure, but just have a look. Remember, what we're trying to do here is we're trying to pick a learning rate value where the loss decreases the fastest or the most. So what part of this graph is the loss decreasing the most? So have a think about that and press play when you're ready to go. How'd you go? Well, I'll tell you the methodology. To figure out the ideal value of the learning rate, or at least the ideal value to begin training our model with, the rule of thumb here is to take the learning rate value where the loss is still decreasing, so maybe here, but not quite flattened out like it looks here. And it's usually about 10 times smaller than the bottom of the curve. So in our case, our ideal learning rate would be somewhere in this section here. So it ends up being between 0.01, so 10 to the -2, so this value, and 0.02, so it'd be about this value here. Now, I actually did prepare something that highlights this a bit better earlier. Finding the ideal learning rate. Here's the code that we ran. There's just our plotting code. Boom. This is what I was talking about. So this is the lowest point on the curve, somewhere down here. But remember, the ideal learning rate is somewhere about 10 times smaller than that. So we have to go back here. So it's somewhere in there. Now, if we go back, if we said that the ideal learning rate is 0.01 or 10 to the power of negative 2, what was the learning rate we set above here that our model got really good performance? Where's model 8? Wow. We set our learning rate to be 0.01. How phenomenal is that? You could call it a lucky guess, but there's another little heuristic we can go here. We can either find the best learning rate through this methodology here, or we could use the default value learning rate, or just take a guess, because an example of other typical learning rate values are 10 to the power of 0, 10 to the power of negative 1, 10 to the power of negative 2, 10 to the power of negative 3, and 1e negative 4. If we have a look at these, so see here, what do these have in common? They're all multiples of 10. Now, you could have a learning rate that's 0.03, or you could have a learning rate that's 0.25. Realistically, there's a whole bunch of different ranges of learning rates that you could use, but why? Daniel, you give me these values, but you've said your learning rate can be almost anything. The reason why I'm highlighting this is because whenever you use an optimizer, say, let's go TensorFlow Atom. If you use a pre-built optimizer, as we've discussed before, their default parameters are generally pretty good. As in, for most of the time, they'll work pretty well. But for when they don't, well, you've got some other learning rates that you can try here. You could just try hard coding these. Typically, you probably won't ever use 1. You'll start to use below 1. So starting from here and keep going down. Or you can use this methodology to find the ideal learning rate. So up here, by using a learning rate scheduler, have it decrease during training, and then plot the log learning rate versus your model's loss and find the value where, or the learning rate, where the loss curve decreases the fastest. Or in other words, just like this graphic here. So see here, loss decreasing very fast. The ideal learning rate is going to be somewhere between the lowest point in the curve and about 10 times smaller than that point. So have a practice with that. Potentially you could train another model on some other data that we've worked with and find the ideal learning rate. But now that we've found the ideal learning rate, let's fit another model. Actually, you can probably try that before we go there. So pick a learning rate in this little section here, create a new model and fit it to our data, and I'll meet you in the next video. In the last video, we saw how we might be able to find our model's ideal learning rate by the learning rate scheduler callback and starting with a learning rate of a fairly low value and slowly increasing it every epoch, and then plotting the different learning rate values versus our model's loss. And we also discussed that the ideal learning rate is somewhere between the lowest point on the curve, and if we jump back to a region where the loss is still decreasing. So how about we try building a model with a learning rate of, so if we look at this point on the curve, the loss is still decreasing sharply. So that's the value we actually set before. If we come back up to model 8, there we go. So this is the learning rate we used before, 0.01. And then if we come down here, which is the same as 10 to the power of negative 2. So if we go 10 to the power of negative 2. But we can also see that if we go jump up one little notch here, because this is a log scale, remember, that the loss is still fairly sharply decreasing here. So that would be a value of 0.02. So how about we try build a model with that learning rate and see if it can achieve similar results to model 8 that we use this learning rate with in less epochs. Because remember, what does the learning rate code for? It codes for how fast our model should try and update its patterns. The higher the value, the more our model is going to update its internal patterns every epoch. So let's see it in action. let's try using a higher ideal learning rate with the same model as before. So we're going to set random seed, tf random dot set seed 42, beautiful. And then we're going to create the model. We're up to model 10 now. How good is that? Double digits, sequential, wonderful. Now you could probably just jump ahead here if you really wanted to. We're going to have 2 layers that are dense with 4 hidden units and a nonlinear activation, relu. And then we'll do the same for the other layer, tf layers dense, and it's going to have 4 activation. It's going to equal relu, or relu, depending on how you want to pronounce it. And then the final layer, just the same as model 8, dense 1, activation equals sigmoid. And now, what do we have to do next? This is where we're going to compile the model with the ideal learning rate. So the value we've just picked off the curve, so this one here, 0.02, and then we'll put this here. Learning rate we used before, model 8. We'll come here. We're going to go model 10 dot compile. Loss is going to be, what loss are we using? Binary cross entropy. And then we're going to go optimizer equals tf. We have to use the class version of Atom here. LR equals, what are we going to set it to? 0.02. Beautiful, because we said we're picking this learning rate value here. Let's come back down. Metrics equals, we'll just keep everything else the same except we're increasing our learning rate by 0.01. And now let's go fit the model for 20 epochs, because model 8 we fit for 25 epochs, so 5 less than before. Let's see what kind of results it achieves with less epochs. Model 10 dot fit. Actually, I might save this as history 10. That's probably better. History 10 dot fit x train, y train, and epochs equals 20. Let's see what happens. And come down. How did it go? All right, loss equals 0.878 and accuracy is 98.24. So what was our model 8 results? Let's go back. So let's save this 0.9824, and if we come back, so 0.9824, you remember that too. Where's model 8? Are we going too far? Model 8. There we go. Oh, 25, and it's 9749. So 9824. Model 10 has performed slightly better than model 8 on less epochs, so less chances to look at the data, all because we increased the learning rate slightly. So it gave our model 10 a chance to learn patterns in the data faster because they were updating with larger steps. Now, of course, as with every hyperparameter with our deep learning models, that might not always happen, but that's just another example of how powerful tuning the learning rate for your models can be. So how about we evaluate it? Evaluate model 10 on the test data set. Actually, we could have just done this to begin with. Model 10 evaluate x test, y test. Wonder how they perform differently on the test data. 99, beautiful. And then we go evaluate model 8 on the test data. How did this perform? Model 8 dot evaluate x test, y test. So our model 10 gets a lower loss value on the test data set than our model 8, but model 8 gets a higher accuracy value. Now that depends on which one of these metrics you want to optimize for. So again, remember, the metrics you get from the training data set aren't always important as the metrics you get from the testing data set. So this is something you'd want to investigate further depending on what your needs are. And so potentially Our Model 10, just because it's learned faster, doesn't mean that its eventual performance on a test data set or unseen data will turn out to be better. So this is where it takes a little bit of trial and error to figure out which model is ideal for your use case. Now, how about we finalize this Model 10 with the ideal learning rate and just see how the predictions look. So I'm going to go plot the decision boundaries for the training and test sets. So plt.figure, fig size equals 12.6. Wonderful. And then we'll get a subplot going. That's 1, 2, 1. And then we'll do the training data first. We'll set up the title there. And then we'll bring in our trusty function, plot decision boundary. And that takes in model 10. It'll also take in xtrain first. We need an underscore there. And then it'll also take in ytrain. And then we want to subplot again, 1, 2, 2. So again, this is row 1, column 2, or 2 columns. And this is section 1, so the first one. And this is 1 row, 2 columns, and the second section. So we'll see what that looks like in a second. plt.title is going to be test. And we want to bring in our fancy function from above, model 10, x equals xtest, and then y equals ytest. Beautiful. And then plt.show. Binary classification, wonderful. So again, our Model 10, using an ideal learning rate that we picked off the loss curve, gets basically perfect predictions on the training data set and the test data set. And see, this is what I was talking about before with the subplot function. We want 1 row, 2 columns, and this first plot, train, is the first element here. And this test plot is the second element in the subplot. So with that being said, we've explored a few ways to evaluate our classification models. We visualize them, but there are a few more classification evaluation methods that we should really be looking at. So let's have a look at those in the upcoming videos. So far, we've seen a few visually rich ways to evaluate our classification models, but let's have a look at a few more evaluation methods that we can use. Now, these are some of the most common evaluation metrics that you should have in your machine learning and deep learning toolbox to evaluate your classification models. So let's have a look here. They've got a key, TP equals true positive, not toilet paper, TN equals true negative, FP equals false positive, and FN equals false negative. So let's have a look. We've got metric name, accuracy. We've seen that one. There's the formula there. True positives plus true negatives. So all of the true predictions on top of, divided by all of the other predictions. If you wanted to do this in code, the accuracy metric, you can do tf.keras.metrics accuracy. Or if you want to use scikit-learn, it has a accuracy score function in there. Now, when should you use accuracy? Well, it's the default metric for many classification problems. However, it's not the best for imbalanced classes. So for example, if you had 10,000 examples of one class and only 10 examples of another class, and you got a classifier to score 99.999% or something like that, it could just predict that everything is all one class and get that sort of result. So in that case, you probably want to look into using metrics like precision. Now there's a formula for precision here, true positives over the total positive predictions, including false positives there. If you wanted to use it in code, you can use precision. Higher precision leads to less false positives. Let's go to Google and go, what is a false positive? Oh, coronavirus testing. What is a false positive? That's a topic of the moment. What is a false positive? There we go. A false positive is when someone who does not have coronavirus tests positive for it. So you can see where a false positive may have altercations. Oh, it's not a good thing, because if someone tested positive for coronavirus, that could go on to have a whole bunch of adverse effects that you didn't want. So if you're training a machine learning model, deep learning model as well, and you wanted it to predict less false positives, in other words, predicting if someone had coronavirus when they actually didn't, you'd probably want to optimize for the precision metric. Now, there's also recall, which is true positives over true positives plus false negatives. If you wanted to use a code, you could use one of these two functions here. Now, higher recall leads to less false negatives. So if a false positive is someone being predicted as having coronavirus when they don't actually have it, what do you think a false negative is? And what would be the implications there? So the false negative in this case would be if someone was to predict, we did a coronavirus test and I actually had coronavirus, but my test came back and said that I didn't have it. So you could imagine, again, that would have consequences as well. If I had a test that said that I didn't have coronavirus and I go about my life and do whatever I want to do, and then I start giving it to other people, well, then that's not an ideal scenario, is it? So for problems where false negatives are not good for your use case, you want to train your deep learning models to have higher recall. However, you might be thinking, why don't we just increase precision and recall? There's often a trade-off between the two. And I'll show you here. What is the precision recall trade-off? Precision recall trade-off, beautiful. Let's understand precision recall. Where is it? Have we got a trade-off curve? There we go, this is probably it. Unfortunately, you can't have both precision and recall high. If you increase precision, it will reduce recall, and vice versa. This is called the precision recall trade-off. So keep that in mind, that in an ideal case, your model would have high precision and high recall, but usually when you try to improve one versus the other one goes down. So say we wanted high precision, you would have lower recall, and the inverse of that is also true. Another option is to try and improve the F1 score, which is like a combination between precision and recall. So the F1 score is one of the scores that I like. It's usually a good overall metric for your classification models. But again, me just reading these evaluation metrics to you out loud probably doesn't make as much sense as to when you start to code them up and start exploring them yourself. So just keep that in mind. We're just talking about these here. We're just naming these different metrics. It's not until you get to start to use them in practice that you'll really start to understand when to use which. And then finally, another great one is a confusion matrix. So this is particularly helpful when you're dealing with all the way from binary to multi-class classification. You can create your own custom function, or scikit-learn has a built-in confusion matrix function. So when to use? So when comparing predictions to truth labels to see where the model gets most confused. It can be hard though to use with very large numbers of classes, as we'll see in a future project. So keep these in mind. Again, this is just a slide. In the upcoming video, we're going to have a practice implementing a confusion matrix. But for these ones here, the accuracy, we've already done this during our model training. So for precision, recall, and F1 score, your homework for this video is to dive into the TensorFlow or scikit-learn documentation for each of these three. And then I'll see you in the next video. We'll start applying some of these metrics or evaluation methods to the problems we've been working on. In the last video, we introduced some more classification evaluation methods. Now again, these are some of the most common and the ones you definitely want to keep in your toolbox. So make sure you screenshot this or take a note down of these metrics, because they're probably going to be the ones you most commonly see with classification deep learning models. We didn't write much code last video, so let's make up for that. We'll go back to our notebook here and all right, another heading here, more classification evaluation methods. And so alongside visualizing our model's results as much as possible, there are a handful of other classification evaluation methods and metrics you should be familiar with. And because this is not a markdown cell, it's going to keep going. That is all right. we'll just put a little few dot points here. We'll just replicate that slide that we had. We had accuracy, which is probably the most common, and then precision. A higher precision leads to less false positives. And then we had recall. A higher recall leads to less false negatives. However, there is the precision recall trade-off, which is an important concept to be aware of. There's the F1 score, which is a combination of precision and recall, and usually a good overall classification metric. And then, of course, there's the confusion matrix, which is another visual way of looking at things. And then finally, this is not TensorFlow specific, but it is also another way that you can see everything, classification report from scikit-learn. Is that on the slide before? I don't think so. We can put this one here. I'll go here, classification report, scikit-learn. The good news is a lot of these classification metrics all have a very similar principle. They take in some true values and they compare them to our model's predictions. That is the crust of whenever we're evaluating a model. What were the true values the model should have predicted? And what were the values that it did predict? Let's compare the two. So I'll just put this little link in here. For the rest, the previous slide that we looked at shows the code examples that you can use. So let's start off with accuracy. I mean, our model has already used it because we passed in accuracy up here as the metrics. Let's write some code to make that look a little bit better. So we can go here. We've got check the accuracy of our model. And we got loss accuracy equals model10.evaluate. And we're going to evaluate it on the test data set. And then we're going to print, we'll make this a little bit prettier. So model has, or just model loss on the test set. That sounds a bit better, doesn't it? And then we're going to do, because it's an F string, we can pass that, beautiful. And then model accuracy on the test set. Wonderful. And then we can just, because we're going to set accuracy up here, let's times that by 100. And then we'll just put, we'll shorten it to 2 decimal places. Will this work? I hope so. There we go. Okay, so see what we did there was we just evaluated it on the test data set, and then we found out the loss, because that's what our model is going to return with the evaluate function. So the loss is there, and then the model accuracy, it comes out in this dot point notation. We've just adjusted it here to be more visually appealing. So what should we work on next? How about a confusion matrix? So what we do is we'll end this video here and we'll come back to the next video and we'll see how we can make a confusion matrix with our model. Last video, we left off with the question, how about a confusion matrix? We checked out the accuracy. Again, if you want a little bit of homework, you can check out our model's precision, recall, and F1 score. Before we create a confusion matrix, let's see what the anatomy of a confusion matrix is. So this is what we're going to be working towards creating. So it's a matrix, so it's got rows and columns. And on the y-axis of a confusion matrix are usually the truth labels. So this is what ideally our model did predict, but on the x-axis is what our model actually did predict. So inherently, what happens when you lay it out like this is that on the diagonal are the correct predictions. In other words, the true positives and the true negatives. So you might be wondering, well, what's a positive and what's a negative? Well, in the case of binary classification, a true positive is when the model was supposed to predict 1, when the truth is 1. And a true negative is that the model predicts 0 when the truth is 0. So knowing this, you might have guessed that the ones outside of this diagonal are the false positives and the false negatives. In other words, a false positive is when a model predicts 1 when the truth is 0, and a false negative is a model predicts 0 when the truth is 1. So again, this is just seeing the name of things. Let's code this up and see what it looks like. Let's go back to the previous slide and see where the code is at. Confusion matrix, what is the code? Custom function or sklearn metrics confusion matrix. All right, let's not reinvent the wheel to begin with. Let's bring in scikit-learn's confusion matrix. So scikit-learn confusion matrix. Metrics.confusion matrix. Beautiful. Okay. Is there an example? All right, so example from sklearn metrics, import confusion matrix. We need true labels, we need some predictions, and then we just pass it to the function. Wow. Okay, let's try it out. So create a confusion matrix. So from sklearn.metrics, import confusion matrix. Wonderful. Then we need to make some predictions. How do we do that with our trained model? So we'll save them to ypreds equals model 10 dot. How do we make predictions with a trained model? If you guess predict, you'd be correct. So we'll predict on the test data set, and then we can create our confusion matrix. Oh, how good is that? Oh, I love scikit-learn. I love TensorFlow. Some beautiful, beautiful code libraries out there. So that's all it is. We've got the Y test, which are our test labels, and our model's predictions. Let's see what the confusion matrix looks like. Oh no, what's happening? No module named sklearn. Oh, typo. Standard sklearn.metrics, import confusion matrix. This should work. Oh no. Classification metrics can't handle a mix of binary and continuous targets. What is happening here? Well, what do we do when we face value errors like this? We have to inspect what we're trying to predict on. So what does Y test look like? Maybe we view the first 10 values. Okay, so that's what Y test looks like. What do our preds look like? Do they look the same? Ah, I see where the trouble is. Look, this is why we're getting a value error. Classification metrics can't handle a mix of binary and continuous targets. So our test values are in binary form. So it's 0 or 1. Whereas our predictions are in continuous form. So they're not 0 or 1. So what should we do here? What do we have to do to compare our test array and predictions array? Well, we're going to have to convert our predictions array into zeros and ones. But what even are these values here? Well, these are called, let's write this down. Oops, looks like our predictions array has come out in prediction probability form. So this is the output. We'll make that in bold. So the standard output from the sigmoid or softmax, as we'll see later on, activation functions. So what we're going to have to do is convert them so they're in prediction probability. So this is a value that the model has output. So the closer the value is to 1, the more the model thinks that it's a 1 label. And the closer the value is to 0, the more the model thinks it's a 0 value. So out of the knowledge that we've learned with TensorFlow so far, is there a function that we can use to potentially round these values, there was a little hint there, to their closest integer value? So for example, if one of these was, let's see if this actually outputs 9.852. I'm not going to type out the whole thing because that's going to take way too long. What does this actually look like? There we go. So is that closer to 0 or 1? Now you might be wondering, of course it's closer to 1, so this one would go to 1, right? And then the same would be for this one, and then the same would be for this one. And then we might have to go on for a while before we find a 0. But you might be wondering, what's the cutoff? Well, the cutoff is 0.5, so anything higher than 0.5 will go to 1, and anything lower than 0.5 will go to 0. However, this is a value, again, you can tune. But for simplicity's sake, we're not going to use that for now. We're going to just convert our prediction probabilities to binary format and view the first 10. Now again, I want you to try and figure out this yourself. How could we round these to 0 or 1 using TensorFlow? If you guessed, we use tf round, or perhaps you already knew that. You're like, Daniel, come on, I'm about 50 videos into using TensorFlow. I know this stuff already. We can go, boom. What does this look like? That's what we want. That's looking more like what our test labels are. So remember, whenever we're comparing things, again, one of the biggest issues that you'll run into is your tensors or your data types being of the wrong format. So all it is about thinking about how you can get them into the right format. So that's what we want. So this is what you'll often have to do with a classification problem. The outputs of your model will come in prediction probability form, and you'll have to convert them to human readable form. In other words, integer form. Now, let's see what our confusion matrix looks like. So let's create confusion matrix y test, and then we want to go tf round y preds, and we're off. Okay. So we got down the diagonal. If we go back to the anatomy of our confusion matrix, let's see. All right, so we've got the same values here, but this isn't as pretty. This is just an array. What we might do in the next video is prettify our confusion matrix to look something like this. We know what the y-axis is. We know what each row is. We know what each column is. We know what the x-axis is. So we can look at this one, but it's not the ideal type of confusion matrix. I mean, if you imagine you were trying to share that with a colleague, what is even going on here? So next video, we'll see how we can prettify our confusion matrix. So in the last video, we made our first confusion matrix. However, we said that it's nowhere near as pretty as the confusion matrix we have here. So how about we write this down? How about we prettify our confusion matrix, because there needs to be more beauty in the world. And excuse me, I'm getting a little bit poetic here, but code can be poetic too. So the function we're going to use, or the code we're going to write, is, I'm going to put a little note down here. So the confusion matrix code we're about to write is a remix of scikit-learn's plot confusion matrix function. Now we've got this up here. So if you look into this, we can click on the source code and we could follow through with that. Fairly extensive source code. Scikit-learn is beautifully documented. You can go through that. I tried out this plot confusion matrix function and I found out it only works with estimators. So a scikit-learn model is referred to as an estimator, whereas we want to use TensorFlow. So we want to adapt it to our TensorFlow code. So you'll often run into this, right? You'll often run into, it's like where you want some sort of functionality, but it exists somewhere else. But to get it working for your use case, you kind of have to tailor it. So that's what we're going to do here. So just follow along. And we're going to make a pretty confusion matrix with this here and with our TensorFlow model. So let's set up a fig size just so we can use this again. Now, because we're going to be writing a fairly extensive amount of code here, what's our principle? Whenever we're writing something, if you get stuck or you're not sure what's going on or my explanation isn't as great as it could be, always pause and rewrite it yourself and see what happens. That's what I do whenever I don't understand something. So we want to go, we can just create our confusion matrix just like we've done up here. So nothing new so far. Y preds, beautiful. You might have noticed I've imported itertools. We'll see where that comes into play in a second. We're also going to create a little normalized feature. So if we come back here, this is how we're going to get percentages here. Right, so this label, 98% of them are correct and 2% are incorrect. This confusion matrix works out well because we have 100 examples. Might be different depending on the amount of samples you have for each label, but let's not get distracted, Daniel. Let's code. So we're going to go cm as type float now, because remember our confusion matrix so far is just an array, a very non-pretty array that is. We can just divide it by the sum to normalize it. Axis equals 1. And then we're going to go here, NP new axis. So this is going to be, this will normalize our confusion matrix. Again, if we wanted to see what that looks like, we could go CM norm. Wonderful. There we go. And now let's go in here. We want to set up number of classes. So we can do this by getting the shape of our confusion matrix. Again, to see what something does, cm.shape. This will be helpful for if we had multiple classes. So right now we're only dealing with binary classification, but what if we had 10 classes? We may see that later on, spoiler alert. So let's prettify it. Got my dyslexia kicked in there. Got my F's and T's mixed up. So we're going to create a figure and an ax using plt.subplots, and we're going to set our fig size to equal fig size. We hard-coded this up above here. You don't have to do that, but I just decided to. And then we're going to create a matrix plot. So cax equals ax.matchShow. So this is a matrix plot. We'll go here, matplotlib matchShow. What does this do? Display an array as a matrix in a new figure window. Beautiful. Again, we're remixing some code from scikit-learn here. So matchShow, what do we want to pass it? We want to pass it our confusion matrix, right? So cm, and then we'll set the color map to equal plt.cm blues. A lot of CMs here. Don't confuse our confusion matrix CM with plt.colormap blues. Wonderful. And then we'll go fig.colorbar cax. Wonderful. And finally, we can create classes. We need to set up a bool. So if we do have multi-class, we want it to do something. And if we do only have binary class, which is what we're working with now, we want it to do something else. So that's why we're creating a conditional. If classes labels equal classes, else labels equal np a range cm.shape 0. Wonderful. So if we have a list of classes, if it exists, we'll set the labels to equal classes. But if it doesn't, which is our current scenario, we'll set the labels to be just a range of our confusion matrix shape on the 0th axis, which is just 2. So it'll be 0 to 1. Wonderful. And now let's label the axes. Ax.set, because we're going to be writing a bunch of labels here. We're just going to use the shortcut ax.set for matplotlib. Confusion matrix, that's a title. And remember, we're prettifying it so it looks like this. That's our title, this is our X label, this is our Y label. So these are the ones that we need. X is the predicted label, and then Y label equals true label. Wonderful. We're also going to set up the X ticks to be NPA range and classes. And then the Y ticks is going to be the same thing, NP a range and classes. That's the number of little dashes that we want to have on our figure. We'll see what that looks like in a second. We can also set the X tick labels to be our labels variable, which in the case of binary classification, it's just going to be the range. If we don't have a list of class names, the labels are just going to be the class integer values. And same thing for the Y tick labels, equals labels. We need to set the threshold for different colors. This will make sense in a second. So the threshold equals cm.max, so the max value in our confusion matrix, plus the minimum. And then we want to divide that by 2. So that's the threshold. So this is going to give our confusion matrix different shades of squares depending on how many values are in there. So a typical confusion matrix is you want the diagonal axis to be really dark where the correct predictions are, and all of the other ones where there's not many prediction values to be light. This will make a lot more sense once we visualize our pretty confusion matrix. So plot, we're going to plot some text on each cell. So we can go for I, J in iter_tools. So iter_tools is going to iterate through whatever we pass it. So we want range cm shape 0, and same thing for range cm shape 1. We're going to go boom, plt. Now this is, we're going to set the text for each square. So ji, this is giving ourselves coordinates, and then we can set up an f string for our confusion matrix for ij coordinates, ij index, that is. We want that. And then it's also going to be, and we want in brackets, cm norm, again the same locale index, times 100. We want 1 decimal point here, f, and then squiggly bracket, fix up the f string, and then percentage. Oh, our bracket's correct here. Fingers crossed. There's going to be an error here somewhere, isn't there? Let's traverse back through. Where have we got an extra? Because we want this to be the same color. Okay, wonderful. Yep, that should be like that. Oh, our f string has ended too early. That's what we want. Wonderful. And now we can have a little comma after that. We want horizontal alignment equals center. And then we want to go color equals white. This is going to be the color of the text if our confusion matrix at a particular index is greater than the threshold. Else, we want the text to be black. Wonderful. And the size can be 15. There's a fair bit going on here. But again, if you're not sure what's happening in any of these lines, remember, break it apart. We've got a lot going on here. This took me a while to remix this function here. So I didn't just pull this out of the hat. Let's see what it looks like anyway. See where our errors appear. Wonderful. Text has no property horizontal alignment. Oh, I have a no N. There we go. Woo! So we've basically just replicated our pretty confusion matrix. See what I meant with the color threshold here? We want our squares with lots of values in them to be darker, and the squares with not many values in them to be lighter. And the more values, we can't really see it with this confusion matrix, but we will see it later on. The higher the values, the darker the shade of the square will get. Maybe if we go confusion matrix, images, there we go. This is a good example. So this is without normalization. So we see here, all these squares are light, and all these squares are darker because they have more values. So with that being said, we probably could increase the text size here. So that's a bit more visual. How about we do that? What do we want to do? We want to set the x-axis labels to the bottom. That's what we'll get to the bottom. See those zeros and ones? We want to get those down there. So we can go x.x-axis, access the x-axis parameter, set label position, and then we're going to just type in bottom. Then we go x-axis dot tick. We want to have the ticks down there as well, correct? And then we want to adjust the label size. We can do that by going x, y-axis, label set size 20. And then we're going to go x-axis, label set size 20. And then we can do the same for the title, x.title.set size 20. Now, of course, beautiful, that's looking way better. Have a go at this. We've just prettified our basic confusion matrix. We've come back up here, albeit it took a fair bit of code. We have this array here, and now it looks like this. Now, of course, we could functionize this. Maybe that's a little task for you. We could functionize this to work with any y-test values and y-pred values. So maybe we look at that, doing that later on, or maybe you could try that now. But as you could see, This is a really great and visual way that we could quickly show someone how our model's performing and see how it does on different classes where it gets confused. Now, our model's doing pretty well right now on our data because, as you can see, the diagonal is very dark. But going forward, it'll make more sense once we work with a multi-class classification problem and make a bigger confusion matrix to see where our model messes up when comparing, say, if we had 10 different classes. So that's where we'll finish this video. We'll get rid of these two cells here. And then in the next video, we're going to start tackling a larger example, more specifically, multi-class classification. So go back through, see if you can turn this into a function. Maybe you want to turn it into a version of plot confusion matrix. So you could do def plot confusion matrix, blah, 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 and see if you can pass it something like true labels and predicted labels and have it come out with something like this. So give that a shot, and I'll see you in the next video. Alrighty, welcome back. I'm super excited for this series of videos because now we're going to start, let me write this down actually, working with a larger example. In other words, or more specifically, multi-class classification. So we'll just make this little heading here. Actually, it's probably worth making it a size 1 heading. So we'll turn that into Markdown. Oh, we've spelt multi-class classification wrong. That's all right. Now, what we're going to do in this series of videos is, so far we've created our own data set. Now, we created a blue and red circle data set, which is a fairly simple data set. And then we went through a whole bunch of different steps to model it. We learned how we can improve our models. We learned about nonlinearity, which is important if we want to model data that is nonlinear, so has different shapes. We learned how we could evaluate and improve our classification models. We learned how to plot the loss curves, find the best learning rate, and a whole bunch more classification evaluation methods. So now to really drive all of these concepts home, let's start with a new problem, a multi-class classification problem. So let's say you were a fashion company and you wanted to build a neural network to predict whether a piece of clothing was a shoe, a shirt, or a jacket. So in that case, you have 3 different options. So let's write that down. When you have more than 2 classes as an option, it's known as multi-class classification. So 2 classes on their own is binary classification, but more than 2 is multi-class classification. So that means, this means if you have 3 different classes, it's multi-class classification. It also means if you have 100 different classes, it's multi-class classification. Now, the good news is, with a few tweaks, everything we've worked on so far in our binary classification problem, we can apply to a multi-class classification problem. We could just look at here to see the steps that we've gone through, or we could just jump back into our presentation and remind ourselves of the steps in modeling with TensorFlow. Oh, I love that little animation. Whew, look at this colorful little picture. So we need step 1 is get data ready, turn it into tensors. Okay. Step 2 is build or pick a model. We've built a lot of models so far, so we're pretty familiar with this, yeah. Fit the model to the data and make a prediction. Okay. Evaluate the model, improve through experimentation, and save and reload your trained model. Wonderful. Let's start with step 1. Let's get the data ready. So I kind of hinted at what kind of data set we're going to be using before. We're going to pretend that we're a fashion company and we want to build a neural network to classify different images of clothing. So to practice multi-class classification, we're going to build a neural network to classify images of different items of clothing. Now, The beautiful thing about this is that we can use the fashion MNIST dataset, which is built in to the TensorFlow.Keras datasets module. So let's have a look. If we go TensorFlow fashion MNIST, beautiful, fashion MNIST, TensorFlow datasets. So the TensorFlow datasets module is up here. It has a whole bunch of different built-in datasets that you can use to practice on your own problems. So they're great to use to sort of get familiar with how a neural network you can build with TensorFlow and get it working before you adjust it to your own dataset. That's a really important concept. A lot of the time in machine learning and deep learning, you'll work on problems that have existing outlines and then slowly adjust them to whatever you're working on. So we've got a description here. Fashion MNIST is a dataset of Zalando's article images consisting of a training set of 60,000 examples, so it's going to be our biggest dataset yet, and a test set of 10,000 examples. Each example is a 28 by 28 grayscale image associated with a label from 10 classes. You could go through that documentation there, or you could just follow along with the code here. To get started with the TensorFlow datasets, we'll re-import TensorFlow as TF, and we'll also get the TensorFlow.Keras.datasets module. We're going to import, oh, that needs to be datasets. We're going to import fashion MNIST. Now, the good thing about the TensorFlow datasets is that all of the datasets, or basically as many as you can, or at least the ones I've worked with so far, which is a fair few, have already been split into training and test sets. So we can go, the data has already been sorted into training and test sets for us. So to import it, we can use tuples. So it's going to be train data, train labels, and then another tuple for the test data and test labels. So we'll set that up as equals fashion underscore MNIST, which is this module we just imported here. And then we'll use the load data method. So of course, if you wanted to see this in the documentation, you could come back here. And the split says that it's already in test and train, 10,000 in test, 60,000 in train. And then there should be an example somewhere of how to import it. I guess not. That's all right, it's somewhere here. Maybe in the overview section. Let's get back to focusing writing code. So we shift and enter that. And it'll download, it'll be pretty quick because it's a relatively small data set and it's stored on Google Storage. Now, to check out an example, we can go show the first training example. We go print f training sample, and I'm going to put it on a new line just so it's nice and neat. We'll go train data, and then we'll just get the 0th index from that. And then I'll get a new line after that. We need to finish that f string. There we go. And we're going to do the same thing for the training label. We'll just do the same index here. Of course, we could have done this randomly, but I'm going to just get one out of there. Because that's one of our first steps, right? Whenever we're downloading data, we want to become one with the data. We want to visualize, visualize, visualize. Okay, so what have we got here? Training sample. We've got some sort of array of numbers. Beautiful. And the numbers are varying from, it looks like from 0 up to about 255. Okay. And then the training label is a 9. All right, so this array of numbers, or this matrix, or this tensor of numbers, represents training label number 9. So if we go here, we look up Zalando Research's fashion MNIST. These are the images that we're going to be working with. So there's 10 different classes of image. We got shoes, we got dresses, we got shirts. Come down. We can get the data from there. Okay, here's the labels. So the labels. Each training and test example is assigned to one of the following labels. So number 9, this is an ankle boot. Wonderful. So this first sample is an ankle boot. Now, of course, we could keep looking at numbers. What else do we want to investigate whenever we're working with a new data set? We want to look at the shape, and we also want to look at what it looks like. So let's do that. Let's go check the shape of a single example. So let's go train data. We need to get the first sample, dot shape, and let's go train labels 0 dot shape. Wonderful. So we've got a 28 by 28 tensor here, and the train labels is just a scalar, so it has no shape there. Now, how about we get visual? Plot a single sample. And come in here. So to plot it, we can import matplotlib.pyplot as PLT. And we go PLT because we're working with an image, imshow, and then we can just pass it a single example. We'll go 0, and because its training label is 9, what should it look like? It should look like an ankle boot. Let's see if this works. Oh, okay. So fairly pixelated here, but you can kind of see the outline of a boot there. And how about we try another one? Wonderful. So that looks like a sweater. And then check our samples label. So if we go train labels and pass it the same index as here, what label does this get? All right, it gets a 2. And if we come back here, oh, it's a pullover. Okay. So I said that this was a sweater. Kind of looks like a sweater to me, but again, depending on what data set you're working with, it will have different labels. So we've gotten pretty familiar with our data. We're probably going to have to set up a little list to index on our training labels. So let's start doing that in the next video, and then we'll slowly keep getting more and more familiar with the data before we start to build a multi-class classification neural network. Let's keep going, getting familiar with our data that we're going to be working with for the multi-class classification problem. So far, it looks like that our labels are in numerical form. And while this is going to be fine for our neural network, we probably want them in human readable form. So what we're going to do is create a small list of the class names that we found on the dataset's GitHub page. And that way we can index onto that list so that instead of just having a train label as 2, this actually reads as pullover. So we'll write down here, create a small list so we can index onto our training labels so they're human readable. Again, this is all part of becoming one with the data that we're working with, understanding what kind of problem that we're working on. So we go here, all I'm going to do is just copy these in the same order. So it'll be t-shirt, top, trouser, pullover, dress. So let's just write that down. Might speed this little section up. Wonderful. Now we've got a list of class names that reflects the actual human readable name, and we've got their labels in integer form, which will be great for our neural network. So let's have a look. How many classes are we dealing with? 10. So again, anything over 2 is classified as multi-class classification. So now we've got our class label names. Let's plot another example. So we go here, plot an example image and its label. We go plt.imshow, and which number or which index should we pick this time? How about we go 17, and then we're going to set the color map to be plt.cm for color map to be binary because this is going to be grayscale. We'll set the title plt.title. Now this is where we can index onto our class names list with train label and the same index here. Or actually, we can probably just create an index of choice variable, boom, so that we can just update that, index of choice. Again, you could probably just set this up to be just a random number generator if we really wanted to. But this is how we're going to plot different examples. Wonderful. So there's a t-shirt / top, and we can do it again. 20, there's a dress, 10, t-shirt top, 100, 2000, there's a bag, And there's a code. Wonderful. Now, again, we could keep going through these and visualize different examples so that we know the data that we're working with. But what's next? How about we set up, rather than just running this cell dozens of times, we set up just some code to plot a bunch of random examples so that we can get familiar with them. Now, with a data set like this, you could probably just look at what it looks like here and start to understand, okay, this is pretty straightforward what it is. It's 10 different types of pictures and they're all grayscale. But if you had a larger data set with 100 different categories and your images weren't grayscale, they had a whole bunch of other details in them, you probably want to have a look at multiple or hundreds, if not thousands of samples before you start building a model. And when I say that number, again, that's an arbitrary number. It's just the number of samples that you start to feel familiar personally with the data that you're working with. That's the most important part. So let's write some code to plot multiple random images of fashion MNIST. Import random plt.figure. And right now we're working with an image data set, but the same would go for any type of multi-class classification data set that you're working with, is to visualize as many samples as you can. So we'll probably loop through 4 samples at a time. We'll set up an ax with plt.plot. Actually, we need a subplot, don't we? Because we want to plot multiple different things. We'll give it 2 rows, 2 columns, and the index can be I plus 1 because we're looping through. We'll select a random index using random.choice, and we'll set up a range for the length of how many training samples we have, which is 60,000. So all this is going to do is just pick a random number in the length of our training data. So it'll be from 0 to 59,999. And then plt.imShow, we're going to show the training data sample that appears at the random index, and the CMAP can equal plt.cm.binary, so it comes out in grayscale. And then the title, what do we want the title to be? We want the class names, and then again we'll index on our training labels where the random index occurs. And we don't want any of the ticks because we don't need them, we just want to see the images. So hopefully this works. We should be able to run this cell and visualize. Okay, shirt, bag, sneaker, trouser, wonderful. T-shirt, shirt, dress, bag. So you can imagine if we went through this is a bit easier than what we just did here. So this is what I like to do whenever I'm working with a fairly large data set, is never underestimate the power of randomness. Is I like to look at samples randomly and just keep going through the data set, start to build an image of what these look like in my own mind before I start to build a neural network that's going to distinguish patterns in them. Now I want you to have a careful look at the data that we're working with. What kind of shape does it take on? Are there many straight lines? Are there any curved lines? How does that relate to what we've learned with linearity and non-linearity? So do you think with this type of data that we're working with, are we going to need a neural network that uses just linear, like straight lines? Or will we need a neural network that's going to have some kind of non-linearity in it? So that's something to think about. But have a play around with this little section here. Become one with the data. Run it about 25 more times so you've seen at least 100 different samples. And then the next video, if we come back to our modeling, we've got our data ready. Luckily, it's already in tensors for us because we've downloaded it from the Keras dataset module. However, oftentimes your data won't be ready, turned into tensors. So we'll tick this step off. Now we're up to building or picking a pre-trained model to suit our problem. So we'll get onto that in the next video. Okay, so we've started to become familiar with the multi-class data that we're working with. Now, let's build a model. So we go building a multi-class classification model. Now, I said earlier, well, we've already built a fair few binary classification models, and I did mention earlier that the multi-class classification model, we're only going to have to tweak a few things to get it to work with our multi-class classification data. So if we go back to the keynote, we look at the typical architecture of a classification model. So we've got multi-class classification over here is what we're working on now. So the input layer shape, same as binary classification, depends on the number of features you have. Number of hidden layers, again, same as binary classification. Neurons per hidden layer, it's the same. We've got another difference here. It's the output layer shape. So for binary classification is one class or the other. Multi-class classification has one per class. For the hidden activation, we can use the same. In binary classification, we use the non-linear function relu. And I asked you in the last video to think about whether or not we might need non-linear activation functions. The output activation, okay, that's different too. For multi-class, we're going to need the softmax function rather than sigmoid. We also need a different loss function. So for binary classification, we use binary cross entropy. But for multi-class classification, we use categorical cross entropy in TensorFlow. And then finally, the optimizer can stay the same, so we can use our trusty atom. All right, let's write some of these down. We go here. For our multi-class classification model, we can use a similar architecture to our binary classifiers. However, we're going to have to tweak a few things. Namely, first of all is the input shape. So what is our input shape? What shape is our data? This is what we explored before. So the trained data sample 0 dot shape. Okay, so our input shape is 28 by 28. So let's write that down. 28 by 28. The shape of one image. Wonderful. And we're also going to have to modify the output shape. What was the output shape? If we come back to our typical architecture of a classification model, the output layer shape is one per class. So how many classes did we have again? Blank class names. Beautiful. So the output layer shape is 10, one per class of clothing. That's what we want. And what else was there? The loss function. Loss function equals, has to be tf.losses.categorical cross entropy instead of binary cross entropy. We'll put that there. And then I think that's all we'll have to do. Beautiful. Because we can keep the other things the same. The output activation. That's what we need to write down. Output layer activation equals softmax, not sigmoid. All right. So with this being known, how about we put together our first multi-class classification neural network model? So we're going to go through the exact same steps that we've been through before. So set random seed, tf random.set seed. We'll give it 42. Wonderful. Let's just try replicate the exact same model we've been using in previous videos. So we'll go create the model. I think we're up to model 11 now. tf caras sequential. Wonderful. And then what did we have? We had two dense hidden layers. tf caras layers dense with 4 hidden units and a relu activation. So we'll just make 2 of those. tf caras.layers.dense 4 and a relu activation. Wonderful. Nonlinear, because this is the answer to the question I posed before. If you guessed that we're going to need nonlinear activation functions for our data, you'd be correct, because it is composed of straight lines and non-straight lines. So that's why we need nonlinear activation functions. For our output layer, this is going to be different, isn't it? We can't use the exact same one. How many output shapes do we need? We need 10. Wonderful. We can do that. 10. And we're going to change our activation from sigmoid to softmax. So we can do it like this, softmax, or we can also do it like this, tf caras activations dot softmax. Now I'm not sure if it's a capital S. Let's look it up. TensorFlow softmax activation. There we go. So I believe we might just be able to put it like that. Let's see if autocomplete helps us out. Softmax. There we go. Wonderful. Now, what else do we have to do? We have to compile the model. As always, compile the model. We're up to model 11.compile. Loss equals, what do we have to change here? We need to change it to categorical cross entropy. tf losses or categorical cross entropy. Wonderful. We can do that. And then we can go optimizer. We don't have to change that. We can do our trusty atom optimizer. We'll leave all the default parameters there. And finally, let's set up metrics. We'll just set as accuracy. Our trusty accuracy. Beautiful. So let's fit the model. And we're going to save this as non-norm history. And you might be asking, why is that? Well, I will reveal all in an upcoming video. Now we can fit directly on the train data and the train labels. And we might go just for 10 epochs. So 10 passes through all of the data. And we're going to introduce a new parameter here to the fit function, which is validation data. So this is where you can put in, we don't have a validation data set, but we already do have a test data set. So what we can do here is at the same time the model is fitting and trying to find patterns in the training data, so the relationships between the training data and the training labels, it can evaluate how well those patterns are on the validation data. But in our case, we don't have a dedicated validation set, so we'll just use our test data here. So this data will remain unseen, and that way we can evaluate how good our model's patterns are that it's learning in the training data are when we use them on unseen data. So let's see how this goes. Oh no, what have we got wrong here? Value error, shapes. The classic shape error. What have we got? Shapes 31, 32, and 32, 28, 10 are incompatible. Where are we getting these shape errors from? 4. So what's 28 plus 4? That's 32. You know what? I'm going to have to introduce a new layer here. And this is a layer that you're going to often need. So it's worth exploring it a little bit. We need to flatten our data. And what does flatten mean? I'm going to give it here. Input. What's our input shape of our data? Input shape is 28 by 28. So the input shape, we're going to pass it here as 28, 28. This is telling our neural network that, hey, we're passing you some images that are 28 by 28. And you might be wondering, what does flatten do? Well, let's explore it. We'll get a new cell here and go flatten model equals, we're just going to create a model with a single layer. tf is sequential. And tf is, of course, if you want to skip ahead and just look up the documentation rather than listen to me talk about what the flatten layer does, you can 100% do that, but I like exploring things by writing code. Because I'm not sure about you, but I tend to read like documentation 3 different times and still don't understand it. When I write the code, I start to understand it. Let's check the shape of this. What is happening here? None 784. Where did 784 come from? I'll give you a little hint. What's 28 times 28? 784. All right. Well, now that we've seen the flattened layer in action, now let's look it up in the documentation. So TensorFlow flatten layer. Flatten layer. Flattens the input. Okay. Does not affect the batch size. Do we have a demonstration here? Okay, so this is the original shape, 1 times 10 times 64. And if we use flatten on that, it's going to turn it into 1 times 10 is 10, 10 times 64 is 640. I see. So what it turns it into, instead of being a 28 by 28 array, it flattens it all so that it's now of shape none 784. Because what you'll often find is a neural network likes everything to be in one long vector. And then we pass that through these other layers here, and we get to the outcome that we like. So our data needs to be flattened. And we'll go here from 28 by 28 to none 784. So if you ever run into a shape error in your neural networks and you find that you haven't flattened your data into one long vector, could be because you're not using a flattened layer as the very first layer of going into your neural network. Some layers can flatten your data automatically, but typically you'll need to tell your neural network that, hey, here's the data, here's my input shape. I want you to compress that, flatten that into one long vector, and then pass it through your other layers. So now that we've flattened our data, let's see if it gets rid of this value error, the shapes that are incompatible. And again, as I said, the shape error is one of the most common errors you'll come across. Oh no! What have we got here? Value error. Shapes 32, 1, and 10 are incompatible. You know what? I think it's our loss function. You might be thinking, Daniel, that loss function is the exact same that we have in the multi-class classification, in the architecture of a classification model. What's going on? Well, there are two types of loss function. Now, one is for if your data is one hot encoded. So if we go, what's our training labels look like? Train labels 0. So our training labels are in the form of integers. So maybe we'll have a look at the first 10. There we go. So 9, 0, 0, 3, 0, 2, 7, 2, 5, 5. Let's have a look at the documentation for categorical cross entropy. I'll just copy and paste that in there. Computes the cross entropy loss between the labels and predictions. Use this cross entropy loss function when there are two or more label classes. We expect the labels to be provided in a one-hot representation. If you want to provide the labels as integers, please use sparse categorical cross entropy loss. So that is where we're getting our value error from now. The shape error is coming because the loss function, categorical cross entropy, now I get confused with this all the time, but this loss function expects our labels in one hot representation. But if we change it to sparse categorical cross entropy, it should work. So let's try that. Sparse categorical cross entropy. Let's see what happens. Oh, yes, look at that. Our neural network is running. Beautiful. So two little tidbits to take away from this is that our binary class classification model that we've used before, this is very similar, this model 11, to all the other models we've been building throughout this entire section, can work for multi-class classification data with a couple of tweaks, namely defining what the input shape of our data is, changing the output layer activation function as well as how many classes we're after, and updating the loss function to reflect the problem that we're working with and also the style that our labels are in. So I wonder if we can one-hot tf.1hot, one-hot train labels depth equals 10. What happens if we do that? There we go. Oh, I wonder if that'd work. Categorical cross entropy, change that. And then we just tf1hot train labels depth equals 10. And then we can do the same. We're going to have to do the same for the validation. This is experimenting on the fly here. Depth equals 10. Man, we need an extra bracket here, don't we? Boom. Our neural network starts to run as well. Wonderful. So let's put a little note down here. If your labels are one hot encoded, use categorical cross entropy. And if your labels are integer form, use sparse categorical cross entropy. This one has tripped me up a whole bunch of different times. Just takes a little bit of practice. So again, oh, typo there. If you get any shape errors with your models, the three things you have to look at: input shape, output shape, and the loss function that you're using. So they're the three main value errors or shape errors that you're going to come across. Of course, there could be more, but they're the three that I most often run into. So how exciting is that? We've already built our first multi-class classification model. let's continue on with where we were in the next video. In the last video, you built your first multi-class classification model. So you should be very proud of yourself. Give yourself a little pat on the back. But there was one thing we kind of forgot to talk about. We did code it, but we didn't really explain it. Is this validation data parameter? So you might have noticed a change in the output of our model training log here. If you see loss, accuracy, val loss, val accuracy, you might have sort of figured out what the val loss and the val accuracy is. If not, that's fine. The loss here with no prefix is the loss on the training data. So how wrong the model is, trying to figure out the patterns between the training data and the training labels. The accuracy here with no prefix is the model's accuracy on the training data. But the val loss and the val accuracy here is the model's loss on the validation data and the accuracy on the validation data. Now this is important because this is the data that a model has never seen before. So it trains on the training data, and then it validates itself to see how good its patterns are on the validation data. So whenever you pass the validation data parameter with some kind of data, you're going to get these extra outputs here. And so this is a way to tell, remember, a model's results on the training data set don't necessarily reflect how it's going to perform in the real world. You really want it to perform well on data it hasn't seen before to sort of get an idea of how it's going to perform in, say, your application or something like that. So right now, our model is getting a score, an accuracy score of about 35%. Now, that's better than guessing because we're working with 10 classes. So if we do 10 or 100% accuracy divided by 10 for 10 different classes. If our model was just guessing, it would get about 10% accuracy. So, okay, we're getting about 3.5 times that, but let's see if we can improve it. First, let's get a model summary. Check the model summary. I want to highlight something else before we move on to try and improve this accuracy, is the input and output shapes of our model, which is a very, very important point. Check the model summary, model11.summary. We go here. So we can see that the flatten layer takes our 28 by 28 images, flattens them into a 784 long vector. It passes through these two dense layers. So dense layer 1 here, dense layer 2 there, and then it gets output into a size of 10 for 10 different classes. So now, do you recall back when we were pre-processing data? We haven't done much pre-processing data with this problem because the data we got from the Keras datasets module, the fashion MNES dataset, is already numerical. However, we spoke about in a previous video the concept of scaling or normalization. If you're not sure, if you can't remember it, that's okay. We're going to go back through it. So we come back to our keynote. I deliberately left this arrow here so that you would think about, what's Daniel missing out on there? Well, number 1 is turn all data into numbers. Luckily, we've already done that. Number 2 is make sure all the tensors are the right shape. Well, we've already been through that too, so tick, tick. Number 3 is scale features. What does this mean? Normalize or standardize. Neural networks tend to prefer normalization. So let's remind ourselves of what that is. Better yet, let's remind ourselves of our training data. Check the min and max values of the training data. Train data.min and train data.max. Alrighty. So 0 and 255. Now, if we said in this slide that neural networks prefer normalization, what is normalization? Well, it's also referred to as scaling. So let's write this down. Neural networks prefer data to be scaled, or which is also referred to as normalized, or depending on what circle you're from. This means they like to have the numbers in the tensors they try to find patterns in between 0 and 1. However, right now our data is between 0 and 255. So how might we get our training data, and we're going to have to do the same for our validation data, between 0 and 1? Well, we can do that by dividing all of the data by the max number. So let's have a look. So write this down. We can get our training and testing data between 0 and 1 by dividing by the maximum. So this is referred to as scaling or normalization. Again, sometimes you'll find different names for different things, but if I use the word scaling or normalization, I'm referring to getting our data set between 0 and 1. So let's go here, train data equals train data, and we'll divide by 255 as a float, because that's the max value, 255. Then we do the same for the test data, equals test data divided by 255. Or actually, what we might do to save the fact that we're not overriding our original variable, we'll do train data norm and test data norm. Wonderful. And then we can check the min and max values of the scaled training data. Train data norm dot min and train data norm dot max. Boom. What do you think they'll be? 0 and 1. Beautiful. Now that our data is between 0 and 1, let's see what happens when we model it. So we're going to actually just we'll change nothing, absolutely nothing, from model 11, except for the data that we're using. So the only thing that it will change is we'll use train data norm and test data norm, and everything else will stay the same. So you can go ahead and try to replicate that before I replicate that in the video. But I want you to think, now that our data has been normalized, it's one of the things that we can tune with our neural networks to make the performance better. What do you think will happen with the different data using the exact same model? It's all right if you're not sure. Let's find out. So now our data is normalized. Let's build a model to find patterns in it. So we'll come here, set random seed, tf random, set seed, and then we'll go create a model, same as model 11. We'll call this model 12 actually. A dozen models, how good is that? tf.Sequential. We're going to know how to do this off by heart. And then we're going to need a flatten layer to get our data from 28 to 28. Flatten. Input shape equals 28, 28. Telling our model, hey, I'm passing you images that are size 28 by 28. And then we'll create our two hidden layers with nonlinear activations, relu, tf layers dense, so that our model can find non-straight line patterns in our data. And then the output layer needs a shape of 10 because we have 10 different classes, and an activation of softmax because we're dealing with multi-class classification. And we can compile the model. We'll go model 12 dot compile. We'll set the loss function. It's going to be tf losses dot sparse categorical cross entropy. Because why? Because our labels are in integer form. I say integer like differently every single time I say it. But if our labels were one hot encoded, we just want to get rid of sparse. The optimizer is going to be tf activations, our trusty friend Atom. Beautiful. And then the metrics is going to be accuracy, which is a great baseline metric for all classification problems. And then finally, we can fit the model. We want norm history. So we saved our model's training history to non-norm history. I said I'd come back to this variable, but this time we're going to use norm history. Model 12.fit on train data norm. And then train labels is just going to be the same thing. We use 10 epochs equals 10. Wonderful. And then the validation data is going to be test data norm, and test labels. Woohoo! Look at us, building multi-class classification neural networks like a boss. All right, do you reckon this will work? What do you think is going to happen? Before we run it, we've normalized our data. That's the only thing we've changed. Have a think about it. And I'm going to run the code in 3, 2, 1. Hopefully no errors. Oh, of course. Activations. Activations? Did I spell that wrong? Oh, no, this has to be optimizers. Oops. Honest mistake. Again, what have we got wrong here? Expected float 32 passed a parameter y. Got type string. Test data norm, test labels. Oh, this is an error I haven't seen before. What are we missing out on here? You know what? I believe it's just this simple brackets. Wow. Yeah, so those are the type of errors you're going to run into. Just simple little things like that. That was kind of a lucky guess, but you can spend hours sometimes troubleshooting them, so don't worry if you get stuck on something like that, because even I myself, who have built a fair few of these models, still run into simple syntax errors like that. But look what's happening here. 10 epochs, we've run this just as before. What has changed between our two models? The data. We've normalized it. That's it. The val accuracy has shot up from 0. What was it before? Come back up here. Has shot up from 35% to 70 to 80%. So it was over doubled. So almost 2.5 times as good. Now all we did is we normalized our data. So that's something to keep in mind. So let me write this down as a key. So we'll get our key emoji out. All right here. Note, neural networks tend to prefer data in numerical form as well as scaled/normalized. So numbers between 0 and 1. Beautiful. So just by normalizing our data, we got a fairly dramatic increase in performance. How cool is that? So that's something I want you to keep in mind. So in the next video, what we'll probably do is we've saved our norm history, our model training history from norm history, as well as norm history up here. So that's a bit of a tongue twister to say. So if you want to, you can have a go at plotting those loss curves between each other from the history variables and see how they look compared to each other. We've trained two neural networks using the exact same architecture, but except one was trained on non-normalized data. And then we said neural networks tend to prefer data in numerical form. That's definitely needs to be in numerical form. But they also prefer it to be scaled/normalized. In other words, the numbers need to be between 0 and 1. So let's compare the loss curves of each model. In other words, the loss curves of normalized data versus non-normalized data. So we'll grab pandas, we'll import that. And then we'll plot the non-normalized data loss curves. So PD data frame non-norm history dot history, and then we'll go dot plot, give that a title of non-normalized data. Beautiful. And then we can plot normalized data loss curves, PD.DataFrame, and we want norm history.history, or plot title equals normalized data. Wonderful. Let's see what this looks like. Wow. So from these two plots, we can see how much quicker the model with normalized data improved versus the model with non-normalized data. So have a look at this. If we go here, our model with non-normalized data, the loss decreased and then it kind of flattened out there. But with normalized data, our model's loss dropped. It even started at a lower value than what this model finished with, and then it kept decreasing as it kept going. And the accuracy Who knows, maybe if we train this for longer, it will keep going. The same with this one actually, but it would probably take a fairly long time to find the same level of results that our normalized data found. Another key point to remember is when making comparisons of different models. So we'll put down here, where's our key emoji? When comparing the results, so we'll write down note, the same model with even slightly different data. So this is the same data set. All we've done is we've just turned it from non-normalized to normalized. So it's the same data that we're working with, but the same model with even slightly different data can produce dramatically, let's get really dramatic here, dramatically different results. So when you're comparing models, it's important to make sure you're comparing them on the same criteria, e.g. same architecture. This is the comparison we're making here, but different data, or same data but different architecture. So that's something to keep in mind here when you're comparing the results of different models. Keep your comparisons to only comparing as smaller variables as possible. What I mean by that is don't change like 10 things and then compare one model to the other. Change one thing and then compare the results from one to the other so you know what change is making the difference in performance. So with that in mind, when we're pre-processing data, let's come back here. When we're getting our data ready for our neural networks, we need to turn it all into numbers. We already started with that with fashion MNest. We had to make sure all of our tensors are in the right shape. We did that using the flatten layer, so the input shape to our neural network, as well as the output shape of our neural network. And number 3, scale your features. So normalize or standardize them. Remember, neural networks tend to prefer normalization. With this being known, how about we try tweak another one of our neural network hyperparameters? Let's see how we might find the ideal learning rate, just as we have before in a previous video, and see what happens to our neural network training. We've seen how even slightly changing the data we input to our neural network can produce dramatically different results. How about we try, let's go in here, finding the ideal learning rate and see if that changes anything. So just as we've done before in a previous video, we'll set the random seed. So the ideal learning rate is the learning rate value where the loss decreases the most. So to do that, we're going to set up the exact same model that we did before. Create model. We're up to model 13 now. tf.Variable sequential. And we had a flatten layer. tf.Variable layers dot flatten. Wonderful. And the input shape equals 2828. Of course, that will change depending on the data you're working with. tf.Variable layers. We need a dense layer. I'm spelling everything wrong today. Activation is going to be relu. Again, I'm not sure what's going on with the code editor. I want to keep our code nice and neat, right? So if someone else had to read this, they're not going, holy gosh, what did you even write here, Daniel? And don't forget, when you're writing code, that someone else could be you just later. Layers, dense, we need a layer with 10 output units and an activation function of softmax because we're dealing with multi-class classification. We can compile model 13.compile. Everything is going to stay the same as above. Loss function, we're using tf.Variable losses sparse categorical cross entropy. The optimizer is our trusty friend Atom. Optimizers.atom. Wonderful. And the metrics, we're going to use accuracy. Boom. And now we're going to fit the model. Oh, what do we have to do first? I forgot a step. I'm too used to going create, compile, fit. We need to create the learning rate callback. So LR scheduler equals tf.Variable. Do you remember how to create a callback? We need a callback and we need learning rate scheduler. And we're going to go lambda epoch. Let's start at, what can we start at? 1, e, -3. Let's start at, yeah, -3 for now, because our model's already performing pretty well. So we'll start there, epoch divided by 20. So that just means, remember, this just means start at this value here and slowly increase the learning rate every epoch by 10 to the power of epoch divided by 20. And to fit the learning rate, we can go fit lr history. We'll create another history variable. Model._13 fit. We're going to use train data. We'll fit it on the normalized data and train labels. We're going to go epochs. We'll go about 40 this time. And then the validation data, of course, is going to be test data norm and test labels. And then finally, the callbacks is LR scheduler. Wonderful. So this should work. Fingers crossed. Woohoo! There we go. Okay. So this is going to take about 3 seconds per epoch. So what's that? Times 40, 120 seconds. So I'll come back. I'll speed this up, and I'll come back once our model has finished finding the ideal learning rate. Alrighty. Looks like our model has finished. Let's see what's happened here. Okay, so it looks like it ends up on a pretty, not as great validation accuracy as what it once was. We get a pretty good range of values here, but let's not look at just this training output. How did we do it before? We plotted the learning rate decay curve. So let's do that again. Plot the learning rate decay curve. So we want to import NumPy as MP, import matplotlib. We've already got these in our notebook as before. However, if you were continuing on from this, we'll just re-import them just for completeness. LRs equals, what did we do before? 1e -3 times 10 to the power of NP A range 40, because we use 40 epochs divided by 20. And actually, we don't even need to use NumPy. Let's just use TensorFlow. Stick in the spirit of using TensorFlow. And we're going to plot. We want to semi-log x because we want our learning rate to be on a log scale, ls, and then find lr history, our history variable from up before, dot history, and we only want the loss component from the history. And then we should make our plot pretty. So we'll add x label, this is a learning rate, and the y label is going to be the loss, and then the title can be finding the ideal learning rate. Let's see what this looks like. Alrighty. So we can see when it started off at 10 to the power of -3, the loss decreased fairly sharply, and then it kind of plateaued all the way up to 10 to the -2, and then the loss just sharply increases as it gets closer to 10 to the -1. Now if we come back to our keynote, where is our finding the ideal learning rate slide? There we go. So the ideal learning rate is where the loss is decreasing sharply, find the lowest point on the curve, and then go back a little bit. Alrighty, so let's do that. So the lowest point on the curve is about here. Then if we went back a little bit to where it's still sharply decreasing, I would say, you know what, 10 to the -3 is 10 to the -3 is probably our ideal learning rate, which happens to be, what optimizer are we using? We're using Atom. So as I said, this is proof, look at that, 0.001, that the default parameters for a lot of the different optimizers and other functions in TensorFlow are pretty darn good. So looks like for our problem in particular, the ideal learning rate is just the default value for Atom. So with that being said, for completeness, let's refit a model with the ideal learning rate. So let's refit a model with the ideal learning rate. And we'll go here, set random seed, tf random.setSeed, 42. Oh, I don't want the @ symbol. Getting ahead of myself, pressing the shift key. All of the keys are chef keys because what are we doing? We're cooking up neural networks. That's what we're doing. tf is sequential, wonderful. Now we come over here. tf we have to flatten our data from 28 by 28 arrays or tensors into a vector of 784. In other words, 28 by 28. and we go tf.layers_dense, just the exact same as what we're doing before. Activation equals relu. We'll do another hidden layer. Layers dense for activation equals relu. Wonderful. And then we can come down here, tf.Keras output layer. What does our output layer need? How many classes do we have? We need a hidden unit for every class, and we also need an activation function that is not sigmoid, Daniel, come on, softmax. Thank you for catching me on that one. And we're going to compile model. Model.compile. What's our loss function? tf.Keras losses. We're dealing with integer values, so we need sparse categorical cross entropy. When would we use just categorical cross entropy? If our labels were in one hot encoded form. Now our optimizer, we actually don't even have to change anything here with our optimizer, but we will, just because we spent all that time finding the ideal learning rate, so we might as well put it in there. LR equals 0.001. So again, the default learning rate for Atom is actually 0.001. We can check that by looking at the doc string. Wonderful. And then we can set up metrics equals accuracy, and we can fit the model. Let's save this to just history 14, so we're keeping track of what we're doing. Model 14.fit, train data, train labels, epochs. This time, how about we go 20 epochs? We found kind of what the, oh no, we forgot the normalized data here, because remember our model performs much better on normalized data. We'll go the normalized data. We've got the ideal learning rate, which we actually didn't have to change anything for Atom, but we'll fit for a bit longer this time because we've worked out that our model is doing pretty good. So maybe this time the thing that we'll tweak is how long it looks at the data for. Validation data equals test data. We need to do this as a tuple actually. Test data norm and test labels. Wonderful. Let's fit that. Shouldn't take too long. Invalid syntax, of course. Oh, did you catch that? I didn't catch that. Wonderful. So I'm going to let this fit, but this should turn out to be a fairly well-trained model with close to the ideal learning rate and performing pretty well. So we've got a couple more options based on what we've done in the previous lectures. We can evaluate and improve our classification model. So we've done a bit of improving. So it's probably now time to, once this is finished fitting, is to start evaluating it with some techniques that we've used before. So I'll let this run through, and then I'll see you in the next video. We'll start to run some more evaluation methods on our multi-class classification model. Welcome back. So now that we've got a model trained with a close to ideal learning rate and performing pretty well, let's check back in with our workflow and see what we should do next. So we've got build or pick a pre-trained model. We've kind of done that. We've definitely got our data ready, turned it into tensors. We fit the model to the data. We haven't quite made any predictions yet, but making predictions is kind of synonymous with evaluating the model because, again, what happens during evaluation? We compare what the model should have predicted with what the model actually did predict. We've actually already improved through experimentation as well. So this is another key point to highlight here, is that although this is kind of like a linear step-through way to do things, this is just like a rough overall guideline to steps in modeling with TensorFlow. You can always jump back and forth through different steps and suit them to whatever problem that you're working on. With that being said, let's make a little heading here. Evaluating our multi-class classification model, and we'll turn this into Markdown, and let's put in here a couple of things that we could do, or actually make this sound a little bit better. To evaluate our multi-class classification model, we could, what are some things that we could do? Evaluate its performance using other classification metrics, such as a confusion matrix, assess some of its predictions through visualizations. That's always a fun one. We could improve its results by training it for longer or changing the architecture. Now this isn't really evaluating, but that's just another step that we could do now. And then, of course, referring back to our steps with modeling in TensorFlow, we could save our trained model so that we could use it later. So we'll put that there just so we know. Save and export it for use in an application. Wonderful. How about, in terms of sticking with evaluation, we go through this. Oh, and I've made a typo. Assess should have a double S on the end. We go through the top two. So we'll write down here. Let's go through the top two. So the first things first is create a confusion matrix. Now we've actually got some code up here that we did with the binary classification problem. Evaluating and improving our classification, that should be model, but let's find, where's the confusion matrix code that we had before? It should be somewhere up here. Far out, we've written a lot of code. Here we go. So this is our remix of scikit-learn's plot confusion matrix. What we might do, instead of typing that all out again, I might just break my rule here of writing code, and I'm just going to copy everything that's in this cell, and I'm going to come down to evaluating our multi-class classification model. This is why it's handy to make headings here, you know, so it really lays out your work so you can just jump between different sections. Create a confusion matrix, and have an idea. Why don't we functionize this? Because I kind of issued that as a challenge in a previous video. It'd be cool if we could actually go through it together. So from sklearn metrics, import confusion matrix, just in case we don't have it. We want this to run as a standardized cell. Now, to functionize this, what should we call it? Let's call it make confusion matrix. And because the whole premise of an evaluation function or a confusion matrix in general, this function here, is comparing the test labels with predictions. At a bare minimum, our make confusion matrix should take in test labels, but I believe scikit-learn calls them, is it yTrue? Yeah, let's make it yTrue, so we stick with theirs. And is it also ypred? Yeah, ypred, yTrue. And then the classes, we're going to set that equal to none, because if we want a list of classes, we can set it there. And then what else should we set? We've got the fig size, we've hard-coded that. Let's hard-code that into here. 1010, wonderful. Then what else is there? Oh, we could do the label size. Why don't we just do the text size? Text size equals, we'll set that to 15 by default. Okay, that should be some good parameters there. We'll have to tab all this across. Tab, so it's part of the function. And then now what do we have to update here? So confusion matrix, this is now going to be yTrue. And then our preds are going to be ypred, wonderful. And then fig size equals fig size, that works there, so we can get rid of this. Yes, yes, wonderful. Classes equals, we're gonna have to set that to, I don't think we need that anymore. So set labels to be classes. So if classes exist now, the labels should be the class names, yes. Else they don't exist. It should just be a range of how big our confusion matrix is. Wonderful. Anything else we need to change? We could change these to text size. Text size. That way, I know I set it as 15 up the top, but we'll just make all the text a very similar size. Why don't we do that? That should work. Text size, and we can adjust it. Size equals text size. Okay. Now all the text should be the exact same size. Beautiful. So now we've got a function, make confusion matrix, which takes in a bunch of true labels and a bunch of predictions and classes. That's what's important. So let's run this, make sure all the syntax is correct. remind ourselves of what our class names are. Okay, beautiful. But what don't we have? We have a function, make confusion matrix, and we could have really put some doc strings here to tell us what the function does, but that's all right. I'll leave that for you to explore. We have some true labels. So this is our test labels, but we don't have any predictions with our model yet. So let's make some predictions. Make some predictions with our model. And we're going to create Y probs for prediction probabilities. You might be wondering, what does that mean? We kind of covered it in a previous lecture, but we're going to reiterate here. So to make predictions, we just go model14.predict, and then we want to make predictions on the test data. And I'll put a little note here. Probs is short for prediction probabilities, because we've got the activation function of our output layer. The outputs of our model's predictions are going to be prediction probabilities. So view the first 5 predictions, and we're going to have a look at Y probs. Oh, what do we get here? Why are these like that? So has it already rounded it for us? That is interesting. So this is, did we set our model to have, let's come back up here, train labels, test labels, sparse categorical cross entropy. Yes. That means it's outputted what label it should be. I'm going to pause the video here and inspect this and then come back to see what's going on here. Now, that took me a while, but I figured out what went wrong here. So I said that probs is short for prediction probabilities, but as we see here, we get whole numbers here. Now, you might have spotted what went wrong. Our model predicted on the wrong data. Now, this is a very important point to highlight here, is that we want our model to predict on the same kind of data that it was trained on. Now, what's the key difference here? What did we do before with test data and test data norm? That should be the hint as to what we got wrong just before. So here's our test data, and our test data normalized. What did we change? Well, let's have a look at this first example here, test data 0 and test data norm. What did we do? We normalized it, remember? So our test data samples still have values between 0 and 255, whereas our test data normalized have values between 0 and 1. So that's why we get interesting outputs from our model when we ask it to predict on test data non-normalized, but if we passed in test data norm, which is the variable we created before, we get the outputs that we should get. So that's a very key point. I'm going to write a little note here. Even this is a reminder to myself. Let's get a key emoji in here. Note. Remember to make predictions on the same kind of data your model was trained on. E.g., if your model was trained on normalized data, you'll want to make predictions on normalized data. Beautiful. So, what are prediction probabilities? So these are different numbers. Let's get the first one actually. Y probs. We'll get the 0. So the highest number here indicates the index. So we'll get our class names back up. Indicates the index that our model thinks is most likely the value. So I believe it is this last one maybe. So Y probs. We can use the Argmax. Let's use TensorFlow. tf.Argmax for arg maximum, which is going to give us the index where the maximum probability occurs. So all of these are values as to how likely the sample 0 is t-shirt or top, or trouser, or pullover. So the first one here is t-shirt or top, so that's a fairly low number, e to the negative 11. This is even lower, so it's definitely not trouser, or at least in the model's eyes, it's definitely not trouser. So it seems that the highest value is this one here, which should turn out to be about 0.8. So that's the last one. So our sample 0, our model is predicting as ankle boot. So let's have a look here. So NumPy 9, and then if we take that index, tf Argmax, let's get yprobs 0, and then we index on our class names list. With that, we should get ankle boot. Wonderful. Okay, so now let's turn our prediction probabilities from a prediction probabilities array into integers. So we can do that by going, we'll get rid of this. Now convert all of the prediction probabilities into integers. So let's go ypreds equals yprobs.argmax, and we'll go it on the first axis. And then we will view the first 10 prediction labels. Ypreds. Boom. So now our predictions are in the same format as our test labels. So what can we do now? Well, we can compare the two. So I will leave that as a challenge for you, but in the next video, we're going to use our make confusion matrix function to compare these two. And how about you could try another metric? Maybe look into creating an accuracy score as well. See if you can reproduce the accuracy score we got from model 14.evaluate by comparing these two. Wonderful. Now that we've got our model's predictions in the same form as the true labels, let's create a confusion matrix to evaluate our model's predictions. But first, we're going to create a boring confusion matrix using scikit-learn, just so we can demonstrate how valuable our make confusion matrix function is. Confusion matrix, yTrue is the test labels, and ypred is ypreds. So let's see this. It's kind of hard to tell what's going on here, but with our confusion matrix, we know that down the diagonal, we should have the highest numbers. So looks like our model's performing pretty good across all the classes. So the highest numbers are down the diagonal. Now, let's remind ourselves of what an ideal confusion matrix looks like. So the correct predictions, the true positives and true negatives, are down the diagonal. But right now, this is pretty hard to interpret. So if we were to send that to someone, they're probably going, what the hell is going on here? And this is where our pretty confusion matrix comes in. So let's make a prettier confusion matrix. And we'll go make confusion matrix. Yes, yes, yes. yTrue equals just the same as before. Test labels. Ypred equals ypreds. Now we have classes is going to equal class names. That's our list of class names of the fashion MNES dataset. Then the fig size, it's hard-coded as 1010, but let's make it 1515 just to have a little practice. And then text size equals 10. Let's see what happens. Ho-ho! Look at that. I think I'm going to have to zoom out because that's a big dog. Or maybe we change this to 1010. See what happens. Might be the text is too big now. Yes, it is. So 1515 was a good size. So let's go back to that. Alrighty. This one looks much better than before. So this is where you can really see the power of a confusion matrix. See how visual this is? Like you could send this to someone and they'd be like, okay, they'd start to intuitively figure out. So the true label here, let's explore this. For the t-shirt/top. So again, the darker the square, the more predictions the model got right for this class. However, if we come over here, this square is pretty dark. I mean, 16% of the predictions of t-shirt top were shirt. Okay. Well, does it make sense that our model is getting confused between the shirt and the t-shirt/top? I mean, to me, how do you decipher those, you know? And then where's another one? What else is our model getting confused with? So pullover. Okay, again, the darkest squares down the diagonal, that's good, but it's also getting confused a lot with the coat class. So it's predicting coat when it should have been pullover 188 different times. Now, are they similar? Now we're going to have to explore that in a second, but you can kind of imagine pullovers looking similar to coats. And what else is getting confused on? Ankle boot and sneaker. Okay, well, at least for ankle boots, they're a shoe at least. So a sneaker is a shoe. So that kind of makes sense. This is the kind of thing that you'll be doing with your own problems. I see the shirt class gets confused a lot with t-shirt top, pullover. It's to explore where your model is making errors. And what you can do with this information is start to improve your models. So maybe the t-shirt/top class should actually be incorporated with the shirt class. Or maybe we need some more data of actual just shirts so that our model really learns to differentiate it between t-shirts and tops. But anyway, investigate this confusion matrix a little bit more. It's nice and pretty. In the next video, let's go back through what did we say we're going to do to evaluate our model. Let's get visual a little bit more. Assess some of its predictions through visualizations. So the confusion matrix is one way to visually explore it, but it's something else to actually look at a picture and look at the label that our model predicted versus the true label. So let's write some code to do that in the next video. We're going to start this video off with a little key. So let's go here, key, note. So what's our motto, or one of our mottos, is visualize, visualize, visualize. So often when working with images and other forms of visual data, it's a good idea to visualize as much as possible to develop a further understanding of the data and the inputs and outputs of your models. So I've also discussed the power of randomness when exploring your data. So how about we create a fun little function for, let's write this down so we don't forget. How about we create a fun little function for, what should we do? We should plot a random image. We should make a prediction on said image, and we should label the plot with the truth label and the predicted label. Yeah, this is a great way to evaluate our model. So let's do that. First, we'll need random from Python because we want to plot a random image. And now we'll create a function, def plot random image. I often create a lot of these little helper functions. If I want to do something over and over again, I make sure to functionize it so that I can use it multiple times. So we'll pass it our model. Right now, I think we're up to model 14. We'll pass it a list of images we want to inspect, what the true labels are, and the class names. Beautiful. So we'll make a doc string here so it's a little bit complete. Picks, what does it do? Picks a random image, plots it, and labels it with a prediction, that'll do, and truth label. Wonderful. So we need to choose a random number. So set up random integer. We'll go I equals random dot randint between 0 and len images. Oh, we need a comma there. So does that make sense? So I is just going to be a random number between 0 and the length of images, and images is going to be the images we want it to look at. Wonderful. And now let's create predictions and targets. So the target image is going to be images I, we'll just index on our random number. And then the probs is going to be model.predict. So it's just going to take our model here, .predict on target image dot reshape 128 28. So we'll make sure it's in the right shape for our model because we're only predicting on one image here. So our model right now is trained on images in 28 size, but we're telling our model, hey, we're only passing you one image at a time this time. Then we're going to do a pred label equals classes, pred probs, and we want to get the Argmax. Wonderful. And then the true label is just classes, true labels, I. Beautiful. What else do we need? Oh yeah, we need to plot the image. So plot.imshow, we want target image to be the plot, and we'll set it to a binary color map. So it's just black and white. Beautiful. And now let's do something a little bit fancy here, all right? We're going to change the color of the titles. So change the color of the titles depending, if I could type correctly, depending on if the prediction is right or wrong. So how might we do that? Let's just create a boolean. So if pred label equals true label, that makes sense. So if the pred label is the same as the true label, so the prediction our model has made is the same as the true label, yes, we want to set the color green, because green means good, and else the color equals red. Wonderful. And then let's add X label information, and we want prediction / true label. Let's go plt.x label. And how can we do this? Maybe we just do it with a dot format. Pred. What's the pred? Pred. And then we want to change this to, let's put the confidence in there, why not? 2.f. I always get confused when I'm typing out this little section of code. There we go. And what else do we want? We want the true. So the true is just going to be like that. And then chuck a dot format on here. We could have done this as an f string, or could we? Because we have to have a calculation. Yeah, we probably could have. Oh well. That's all right. This will do for now. We want 100 times for the confidence. We want tf reduce max. So in other words, find the maximum value in pred probs. And then we'll just finish off with true label. And then I believe color goes down here. Color equals color. We've definitely got something wrong in this function, but so set the color to green or red based on if prediction is right or wrong. So does this make sense? Plot random image, pass it a model, picks up a random integer, picks a target image from images, then uses the model to make a prediction on the target image. We have to reshape it to be, because it's only one image. The pred label is going to be classes.predprobs argmax, so the index of predprobs, which has the highest prediction probability. The true label is going to be the true labels indexed on I. Yep, that's correct. Plot the image, target image, CMAT binary, yada, yada, yada. We could keep going through that, but let's just run the code, see if an error comes up. Oh no, we're just defining the function there. We haven't actually run it yet. Let's do this. Check out a random image as well as its prediction. Oh yeah. Plot random image. Model equals our current model, model 14. Images equals test data, because that's the test images we want to work with. Test, or true labels, sorry, equals test labels. And then classes is class names. How does it look? Nice. Okay, there we go. So the prediction is coat, 100%. So that's a very high prediction probability. But the true is shirt. Does that look like a shirt to you? Kind of. Let's look at some more. Ankle boot, 100%. True. Sandal. Is that an ankle boot? I mean, that's a fairly pixelated image. That's kind of hard. Come on, surely our model got something right. Prediction coat. True is actually shirt. Wow, that's a bit... See, that one's on the edge to me. As long as our function's correct. There we go, there's one that's right. T-shirt top, 100% true. Wonderful. Oh, what did we also forget here? This should be norm. Oh, come on, Daniel. Remember, always make predictions on the same type of data that your model has trained on. I'm going to write a note here. Always make predictions on the same kind of data your model was trained on. And by the same kind, I mean pre-processed in the same way. All right, ankle boot, yes, that's what we want. Green, show me some more green. Ah, damn it. T-shirt top, it's a shirt. See, this is what I mean. I'm not sure who created this data set, but to me, T-shirt and top is kind of the same thing as shirt. Maybe it's not, maybe it's not. Trouser, yes, that's what we want. Shirt, predicted. Oh, the true is a coat. Kind of. So, as you see here, you could keep going through this for a lot. We could have really just set this up to plot more than one at a time, so we don't just have to keep sitting enter, enter. Maybe that's a little bit of an extension for you, is to see how you could functionize this to plot, say, 4 images, just like we did before when we were exploring our data. So, going through this, I would say do another 20 or so, go through them, and then figure out, does visualizing these predictions here help you to better understand this confusion matrix here? And what I mean by that is, does it start to make sense where the model gets confused? In other words, like, does the overall shape of a trouser relate to pants? Or does the overall shape of an ankle boot, is the model getting mixed up with a sneaker because an ankle boot is a similar shape to a sneaker? Does that make sense? So, we've done a bit of evaluating for our model. How about the next video? We've talked a lot throughout this entire series that our model is learning patterns. So how about in the next video we discuss what patterns exactly is our model learning. So have a little bit of a play around with our visualization function here. See if you can start to get an idea of where the model gets most confused and compare that to the confusion matrix. And then I'll see you back in the next video and we'll check out the patterns our model is learning to make these kind of predictions. We've covered a fair bit. Well, actually, fair bit is probably an understatement. We've covered a lot in neural network classification with TensorFlow. But this whole time we've been talking about how neural networks learn patterns in our data so that we can use those patterns later on. But what exactly do those patterns look like? Well, let's use this video to find out. So first, we're going to crack open one of our models. So find the layers of our most recent model. So if you're not sure by now, take this as me stating it straightforward, is that a deep learning model is constructed of layers. And each one of those layers has a specific role in finding patterns in the numbers that we feed it. So let's have a look at model 14 layers. So we can see we start off with a flattened layer, and then 2 hidden dense layers, and then an output dense layer, because we typically go from this direction, so top to bottom. So this is input, and this is output. And now we can inspect what's going on in a target layer using indexing. So how about we extract a particular layer. I'm going to go with the first hidden dense layer by indexing on 1. Wonderful. So there we've got an individual dense layer there. And now we can find the patterns learned by a particular layer using the getWeights method. So let's try that out. So get the patterns of a layer in our network. So we're going to set this up as weights and then biases. We'll have a look at that in a moment. Model 14 layers 1.getWeights. You can just search this method up if you want, but I prefer to figure out things ourselves. And then we'll go shapes. So we'll view weights, and then we'll also view weights.shape. Okay. So this is what the internal patterns of a single layer, or specifically the first hidden layer of our neural network, look like. So to you, they might just look like a whole bunch of random numbers, and I mean, to me, that's what they look like. But to our neural network, it considers these as the patterns which contribute to the decisions that it makes. So we're working with fashion MNIST data. So the shape of this weights matrix corresponds to the shape of our input data. So remember our input data was a 28 by 28 image. That's where this number comes from. So if we go 28 by 28, and then we remind ourselves of what our model looks like, what our model input shapes look like. So if we see here, this is a 784, the flattened layer to begin with. And then this 4 comes from the number of hidden units in our first dense layer. So that means that for each data point in our input tensor, our weights matrix has 4, because see here, 4, has 4 numbers that it starts to learn and adjust to find patterns in these 784 numbers. So just looking at this off face value can be very confusing. And don't worry if you're not sure of it to begin with. This is the first time we've ever cracked open one of our neural networks. And this is kind of where the term deep learning gets the idea of black box from. As in, when you crack open a deep learning model, you get all these random numbers. If you or I would try to interpret them, we can't really interpret what's going on here, but somehow they correlate to our model finding patterns in the input data. Now, what each one of these values does, so each value in the weights matrix, it corresponds to how a particular value in the data set should influence the network's decisions. Now you might be wondering, how does our neural network even create such values? How does it learn these values? Well, and let's go back to the keynote to see a high-level overview of how this might happen. So we're working with the input data here, which is grayscale images of the fashion MNES dataset. So we have coat, ankle boot, shirt, sneaker. Wonderful. And then we might encode them to, well, we should have actually normalized this data, shouldn't we? We might transform them into a tensor to pass it to our neural network. And then what's going to happen in our neural network, we've seen this kind of overall schematic before, is that it's going to learn the representation. Another word is patterns, features, weights. These can all mean similar things when you're hearing our neural network talk. For now, we're referring to them as weights, but I have been referring to them as patterns. And so what's going to happen is at the beginning, our neural network is going to initialize itself automatically with random weights at the very start. So if we come back, so all of these numbers, the weights, the internal weights of one of our neural network layers are going to start off as random numbers, just completely random. And it does this, we can look at, if we go to the TensorFlow dense layer, it does this using which parameter? There we go. Kernel initialization. Now, a little bit of extension on this video is that you can read into what this is, glow root uniform, but it might actually tell us here, kernel initializer for the kernel weights matrix. So glow root uniform is a form of randomness. So just take that from here. We're not going to dive into what glow root is, but just understand that that's a form of randomness. Now, if we come back, so it's going to initialize itself with random weights in each particular layer. And then what's it going to do? Well, we're going to show it different examples of the data we'd like it to learn. So we might show it images of coats, images of ankle boots, shirts, and sneakers. And it's going to keep looking at these and slowly update its representation outputs or weights and biases into a different kind of tensor, which has come back to here. If we come back to our notebook, this is what it's going to learn over time, these representations, as we continually repeat with more examples. So does that make sense? Our neural network, we feed it input data. It starts off with random numbers, random weights, random patterns, however you want to refer to it. And then as it looks at more and more examples, it's going to go, hey, I'm going to try these random numbers and see if they correlate to any of the patterns in the data. And if they don't, well, the neural network is going to try and correct itself thanks to our optimizer, Atom. And then we're going to repeat it with more examples as we have more data. Then it's going to slowly adjust these patterns to better suit the data as best it can. To eventually, hopefully, it starts to output all correct predictions. That's the ideal case. So let's come back. Now, we've only talked about the weights matrix so far, but alongside a weights matrix is also a bias vector. So let's come down here. Let's have a look. Now, let's check out the bias vector. Let's go bias and biases shapes. We'll go biases and biases dot shapes. So again, this is from a single layer, more specifically the first hidden layer in our current neural network. So we come down. What does this correlate to? Number 4. So this is a bias vector. So there's only 4 here. So it's this 4 here. So that means for every hidden unit in our neural network in the first layer, it has 1 bias vector. Whereas for a weights matrix, this is the difference, the key difference between a bias vector and a weights matrix. A weights matrix has 1 value per data point, whereas a bias vector only has 1 value per hidden unit. And so, what the bias vector does is we'll write this. Every neuron has a bias vector. Each of these is paired with a weights matrix. And so, the bias vector also gets initialized, but this time, let's have a look up in the dense layer. What is our bias initializer? Zeros. So you can kind of intuitively guess what zeros mean. If we come down, what does it say? How does it get initialized? Initializer for the bias vector gets initialized as zeros, at least in the case of a TensorFlow dense layer. Now, where it kind of gets tricky, right, is that sometimes depending on what layer you're using in deep learning, so within the TensorFlow Keras layers module, your weights matrix, or the kernel initializer, and the bias may be initialized differently. However, as you can see, we never actually set these variables. They got initialized by themselves. So this is what I'm saying, a lot of what TensorFlow does for you, the majority of calculations are done behind the scenes. So of course you can dive deep into this as much as you want, and I actually am a big advocate for that. But to begin with, I just want you to focus on writing as many neural networks as possible and just getting them working. And then once you want to know more, start diving into the nuts and bolts of what's going on behind the scenes. So we've said what a bias vector is. Now what does it do? So the bias vector dictates how much the patterns within the corresponding weights matrix should influence the next layer. Okay? So for every hidden unit, there's a weights matrix and a bias vector. So if we change this to 10, how many weights matrices would there be? And the same thing for this one. How many bias vectors? If we change both of these to 10, how many weights matrices would we have and how many bias vectors would we have? Just have a think about that for a second. So this is a key point here as well. How much the patterns within the corresponding weights matrix should influence the next layer. Another big thing about deep learning, let's re-familiarize ourselves with our model architecture. So model 14 summary, what it looks like. Okay, so we've built a few of these. We've built a few deep learning models. So now's right about the time to point out the whole concept of inputs and outputs not only relates to the input layer of a deep learning model and the output layer, it relates to every single layer within a model. So let's go to the keynote and go to the next slide. So this is inputs and outputs layer by layer. So if we imagine this is our model here, very similar to what we've just built, model 14. And if we can create this in a second. But if we imagine we have this input layer that takes in our input data, in our case, which is images 28 by 28, into a tensor. We should have normalized this if we were really preparing our image data correctly. So this is going to take the inputs and they output it to the flattened layer. The flattened layer outputs to the dense layer, or the first dense layer. The first dense layer outputs to the second dense layer. And the second dense layer outputs to the output layer. So for each layer in a deep learning model, the previous layer is its inputs. So this is the crux of deep learning. This is what makes deep learning deep, is that you have multiple layers. And of course, as you added more layers, the deeper the neural network would go. but each subsequent layer does its part to find patterns in the original data and then feeds it on to the next layer. So as you keep going through, the patterns get more and more refined towards the ideal, or hopefully they get close to the ideal outputs that you're after. So let's have a look at how to replicate this. And I believe that will probably be more than enough to wrap up this video. So let's check out another way of viewing our deep learning models. So we can do this with from TensorFlow.keras utils import plot model and see the inputs and outputs of each layer. Plot model, model 14, and show shapes equals true. Beautiful. So this is what we have. As I said, this is inputs and outputs layer by layer. So it starts off the input. The none here is for batch size. We'll tackle that in a future video. Students can look that up if they want. Let's just say we put in 28 by 28 images, so that's the input. Then this layer outputs the inputs to the next layer. And then this layer outputs the inputs to this following layer. And then so on and so on and so on until we get our idealized output, which is this 10 shape here, because that's how many classes we have. Now, we've covered all of this very quickly of what's actually going on. I just wanted you to get familiar with cracking open one of our models. Now, if you want to dig deeper on what's going on behind the scenes here and how these calculations actually happen layer to layer, I've put some resources in the extension section. But otherwise, I think that just about wraps up everything in the introduction to neural network classification with TensorFlow. So, go back through, pat yourself on the back because we've covered an incredible amount. Take a break to let things sink in. And when you're ready, make sure you check out the exercises. So I'll just put this here. Next, check out exercises and extra curriculum. Check out the exercises and extra curriculum to practice and cement what you've learned. I've put in some stuff there to not only practice everything that we've gone through, that's in the exercises, but as I said before, the extra curriculum will help you really dive in to what's going on behind the scenes here. So, with that being said, congratulations on finishing Section 2, Neural Network Classification with TensorFlow. I will see you in the next module. Welcome to Convolutional Neural Networks and Computer Vision with TensorFlow. That animation's never going to get old. Now, before we get into what convolutional neural networks are and what computer vision is, I want you to have a think about something. This is a very, very exciting module because if you imagine computer vision, we're going to be teaching computers to see. So start to think about what you do in your day-to-day life. What are some applications where it might be helpful if a computer could understand patterns in visual data? Now, I want you to let your imagination run wild here. Visual data could be something from a webcam. It could be something from the camera on the front of a car. It could be a security camera. Just start to think of different applications where it might be helpful if our computers could understand what's going on in a visual scene. But before we get into that, let's answer the most important question, and that is, where can you get help? If you run into problems, here's the steps. Follow along with the code. We're going to be coding together. Remember our motto, if in doubt, run the code. And don't worry if I go too fast, you can always pause the video, write the code yourself, and then get back into it. As always, try it for yourself. There's that motto again, if in doubt, run the code. If you want to see the doc string for some information about the code we're running, press Shift-Command-Space if you're using Google Colab. And Command you might have to sub out for Control if you're on Windows. I put Command there because I'm on a Mac. If you're still stuck, remember you can search for it. You'll probably come across resources such as Stack Overflow or the TensorFlow documentation. Very important when you first start reading these two resources because there's so much information there. It can be quite intimidating. But after a little bit of practice, you'll start to be able to navigate through it and understand what's going on. Then, of course, try again. If in doubt, run the code. And finally, ask a question. don't forget the Discord chat. And yes, that definitely means the dumb questions. And I just want to add one more thing to this while we're here. I'm just going to go to Google Chrome and go to debug.link.tf course GitHub. This is going to be also your ground truth for what's going on. There's a little short link. This will be in the resources section, by the way. This has got all of the ground truth notebooks. At the moment, it's still a work in progress, but by the time the course launches, it'll look a lot more better. Here's all the course materials that you're going to need, such as data sets. This is a new one that we haven't seen just yet, but we're going to dig into this throughout this module. So if you want to have a look at the contents, there's the notebook that we're going to go through and replicate, but I won't jump too deep into all of this. Rather, let's get hands-on first and we can see this as we go. So, let's have a look, or let's ask the question, what is a computer vision problem? So as we said before, did you imagine anything of what a computer could be used for figuring out patterns in visual information? Well, in essence, that's a computer vision problem. Anywhere you want to have a computer figure out something or understand what's going on in a visual scene, it can be talked about as a computer vision problem. But let's have a look at a few examples and get specific. So of course, we've had a look at classification problems before. There's binary classification, whether one thing is something or another. In this case, we might want to build a computer vision app called Food Vision to be able to decipher whether a photo is of a picture of steak or a picture of pizza. Spoiler alert, we might be actually building this throughout this module. Then, of course, there's multi-class classification. So is this photo a photo of sushi, steak, or pizza? In that case, it's more than one thing or another. We've seen some multi-class classification problems in the previous module. And finally, another very common one is object detection. So where's the thing that we're looking for? If we have an image here, this is the rascal that crashed into my car and sped off. So this is some security camera footage. What we might do for this is use our regression skills to figure out where this box is, and then we use our classification skills to figure out what's inside the box and find that car. And on the topic of object detection, I just want to show you another use case of where this comes into play. We go here, Tesla Autopilot. This is probably one of my favorite ones. So on the topic of self-driving cars, we zoom in a little bit here. Now if we check out this video, maybe skip ahead a little. If you see what's going on here, all these boxes? Well, that's a form of object detection. And the Tesla car, of course, has multiple cameras on it. And this is what the cameras are seeing. And so all of these boxes here, some form of object that the car's camera has used computer vision to detect. So when I say that computer vision can be used for almost anything you can imagine from a visual aspect, that rings true. That's just one example of what it can be used for. And again, here are some other problems. So let's have a look at what we're going to cover throughout this module. We'll be a bit specific. Well, actually, this is pretty broad. We'll get specific when we're actually going through it. We're going to get a data set to work with. We're going to use the pizza steak data set to begin with, which is photos of pizza and steak. We're going to build a little app called Food Vision. We'll have a look at the architecture of a convolutional neural network, or a CNN for short. So if I say CNN, I'm referring to convolutional neural network, which is one of the most popular computer vision architectures for computer vision. Wow, I said computer vision architectures, sorry. Deep learning neural network architectures for computer vision. We'll see how we can build one of those with TensorFlow. Then we'll have a look at an end-to-end binary image classification problem, looking at how we can build a CNN to classify pictures of pizza and steak. We'll go through our steps in modeling with CNNs, creating a CNN, compiling a model, fitting the model on some data, and then evaluating it. We'll also look at an end-to-end multi-class image classification problem. And finally, we'll see how we can make predictions using the CNN models we've built on our own custom images. Now that's really fun. And how? Well, in the spirit of a cook, of course, we're going to be cooking up lots of code. So let's go have a look at our computer vision inputs and outputs. We've seen this slide before in a previous module, but let's talk about it in the context of what we've just gone through. So we've got our problem, we've got some images of food, and we want to build an application called Food Vision to identify what's in those photos. And so with our machine learning problem, we might have some inputs, a machine learning algorithm, and then some outputs. And in our case, the inputs are numerical encoded versions of our images, and then the outputs are prediction probabilities of which class is most likely depending on the photo. And so in this case, it's got 2 out of 3 correct here. It got the sushi photo correct. It didn't get the steak photo correct, but it also got the pizza photo correct. And our model might learn these from looking at lots of different examples of actual outputs. So actual examples of images and their proper labels. Now, one thing we haven't alluded to is that this machine learning algorithm is often, in the case of computer vision, because this is a computer vision problem, is often a convolutional neural network, or a CNN. So that's what we're going to go through. We're going to look or see how we can build this part here. Now, of course, algorithms here might already exist, but we're going to have a look at throughout this entire module to see how we can build one. And then later on in the course, we'll see how we can use an existing convolutional neural network for our own problem. And again, let's have a look at the input and output shapes of a computer vision neural network for an image classification problem. We might have a picture of a steak here. Of course, there's some eggs in there, but this is a 224 by 224 size image, height and width. We might numerically encode that. That's our inputs into our ML algorithm. Then our outputs are prediction probabilities of some sort. In this case, it looks like our computer vision algorithm has got it correct, being a photo of steak. And so our input shapes might be here, none for batch size, 224, 224 for height and width, and then 3 for color channels. And of course, these will vary depending on the problem you're working on. But our output shape here is 3 because we're working with 3 classes. And if we are working with 3 classes, is this binary or multi-class classification? If you guess multi-class classification, that is 100% correct because there are more than 2 classes. And again, this machine learning algorithm is often a CNN, and we're going to be building CNNs to do this part. So we've spoken a lot about CNNs, but we've only really alluded to the name of them. In the next video, let's check out what exactly is a CNN. Welcome back. In the last video, we spoke a lot about convolutional neural networks. So in this video, how about we answer the question, what is a convolutional neural network? Or in brackets, CNN. So if you hear me say CNN, again, this is just a reminder, I'm probably referring to convolutional neural network rather than the news site. So let's go through this slide. And again, when we first look at it, it's going to be very daunting. Don't worry. We're going to step through this. Let's have a look at the typical architecture of a CNN. This is what we're working towards building. So if we start off, we got here the CNN model equals tf.Variable model sequential. We've seen that before. Now, what we haven't seen before is a bunch of these layers and probably their internal parameters. So let's start to step through them. We might have an input layer, which in our case is tf.Variable layers conv2d, which stands for convolutional 2D, which for 2-dimensional data, such as images that have height and width, that's where the 2D comes from there. Now, this has a bunch of parameters, filters, kernel size, activation, input shape. We're not going to step through them too much for now because we're going to go through these as we get hands-on with coding. But this is an actual convolutional neural network. So let's have a look. What does it do? The input layer takes in target images and pre-processes them for further layers, such as the typical values. The input shape might be the batch size, image height, image width, and color channels. So that's this variable here, the input shape. And again, the input images are target images you'd like to discover patterns in. And of course, the typical values here can be whatever you can take a photo or video, because a video, remember, is just a series of photos played over and over again, of. Then we might have a convolution layer. Actually the same here. tf.Variable conv2d. We've got another one here, tf.Variable conv2d. And it's got the same parameters as above, it's missing this input shape parameter. But we've got the same values, 10, 3, in order. Again, Don't worry too much about what's happening internally here. We're going to write lots of these and get used to them. I just want you to get an overview of what an architecture of a CNN looks like. Now, what does the CNN or the convolutional layer do? This layer extracts/learns the most important features from the target images. And oh, look, I've got a typo there. I'll need to fix that. What are the typical values? Multiple. You can create it with tf.layers conv_xd. Where x can be multiple values. So we've got conv2d here because we're working with images. But as you'll see in later on modules, we can also use conv1d for text data. And then there's also conv3d for three-dimensional data. Then again, we'll go again. We've got the hidden activation. We've seen that before. So this is a nonlinear activation function. In our case, it's typically ReLU for convolutional layers. What does it do? It adds nonlinearity to learned features. We had a look in the previous module at what nonlinearity is. Non-straight lines, because remember, a lot of the data in the world is not just straight lines. We need some curved lines to help us figure out patterns, or better yet, help our neural networks figure out patterns. Then we typically have a pooling layer of some sort. In our case, this is tf.Layers MatMul P2. You might have guessed that 2D is the same. We've got 2D here as the same reason we've got conv2d, because we're dealing with images which are height by width, two-dimensional. And then we've got pool size 2, padding valid. Not sure what those are just yet. Again, we're going to go through those. And what does this layer do? Reduces the dimensionality of learned image features. So as we'll see later on, max pooling, the layer or the pooling layer, if our convolutional layers learn features from images, such as if we're thinking about a car, a feature of a car might be the fact that the hood is a straight line and the wheels are circular. Those might be two features. Again, we don't define these. They are learned automatically by the convolutional layers. So it might learn the most important features from a target image. Then the pooling layer further reduces. So the pooling layer learns even the most important features out of the already learned features. So this layer dramatically reduces the number of calculations a CNN has to see. This is what I'm saying. I'm probably going to say CNN more than I am going to say convolutional neural network, because convolutional neural network is a bit of a mouthful. So the pooling layer reduces the number of calculations a CNN has to make. So that's what makes it really computationally efficient. Then we have a fully connected layer, which is often the output layer. Now we've seen this one before. tf.Layers dense, and the output shape here is 1s. You might deduce from that we're working with a binary classification problem. We've also got the sigmoid activation function here, which is our output activation. Again, this adds nonlinearities to the output layer. Whew. We've been through a fair bit here, but you can go back through this on your own time. As I said, we're going to go through this and have a lot of hands-on experience writing these. I just wanted to show you right at the start what we're working towards building. And now to make this example concrete, this network here, this convolutional neural network, which is actually the same as tinyVGG, which is from the CNN Explainer website. We'll have a look at that in a future video. But if you want to jump ahead, you can also go to this website here. This convolutional neural network will actually work to build a computer vision algorithm to deduce whether these photos are of pizza or of steak. So we'll see how to build that later on. But finally, got a little note here, a reminder. There are almost unlimited amount of ways you could stack together a convolutional neural network. This slide only demonstrates one. Yeah, that's an important point. All of these layers here, this is an architecture called tinyVGG. Again, the details, we'll jump into that later on. But a convolutional neural network is typically a stack of convolutional layers and pooling layers and a bunch of nonlinear activations. So let's have a look at it in terms of the colored block edition. So this might be a simple CNN. We might have some inputs, which are images. We might process those images, in other words, turn them into tensors, split them into different color channels. TensorFlow will help us do this. And then we pass it to this is our architecture here, which is typically some sort of combination of convolutional layers and usually ReLU activation and pooling layers. This could be just one of these, or it could be 10 of these. And then finally, we top it off with a fully connected output layer. And in this case, it's got the prediction correct. We want it to predict pizza, and it's done it. Then we might go to a deeper CNN, which is, again, that's where the deep and deep learning comes from, is when you stack these layers on top of each other. Our input images, pre-process them as normal, have a convolutional layer, a pooling layer, a conv layer, pooling layer, conv layer, pooling layer. That could be a song. Conv layer, pooling layer. I'll stop. And then again, a fully connected output layer. So we've seen enough. We've seen enough pictures. We've seen enough slides. Let's code. I'll see you in the next video. We're going to get hands-on and start to write some computer vision code with TensorFlow. It's time to write some code. So let's open up a web browser. We're going to go to our ever faithful Colab. So colab.research.google.com. And I'll just zoom in a little bit. 150. I'm going to start up a new notebook. Beautiful. I'm going to call this 03 Introduction to Computer Vision with TensorFlow Video. That's what I'm going to call mine. Remember, I got a video tag because these are the notebooks I'm writing during the videos. So what can we give this heading? We'll just write in here, Introduction to Convolutional Neural Networks and Computer Vision with TensorFlow. Beautiful. And we'll give us a one-liner definition of computer vision. So computer vision, how can we do this? Computer vision is the practice of writing algorithms which can discover patterns in visual data, such as the camera of a self-driving car recognizing the car in front. Nice and simple. So the first thing we're going to have to do is, if we want to build convolutional neural network, is to get some data. We need some image data. We need some visual data. Let's make a heading here, get the data. So I said before that we're going to actually build a little application called Food Vision, or an algorithm called Food Vision, to decipher photos of food. We've actually got a data set ready from the Food 101 data set. So let's look at this. There we go, kaggle.com. I'll leave all the links, by the way, in the place where you can find links, wherever that is. So don't worry too much if you're trying to write all these links down, they'll be where you can find them. So long story short, this is the Food 101 dataset. It contains images of food, organized by type of food. And it was used in the paper Food 101. So there's a paper to go along with this dataset, which is often the case with many large public datasets. So it's about 5 gigabytes. So what I've done is I've downloaded this dataset from Kaggle. I've done a little bit of pre-processing on it. If you want to see how that pre-processing took place, there is a notebook in here called Image Data Modification.ipynb. I just got it into the format that we needed in for computer vision problems, which we will see in a moment. But again, that's just a heads up. I've modified this data slightly from how you might download it. And the code to do that is in here. Again, all of the links you need will be where you can find links. But to get our pizza and steak data set, we can copy this link here. Copy link address. So this is a data set that's already stored, I've already created. We're going to import zip file because we download it as a zip file. wget. And then we're going to put in this little link here. This links to a Google storage bucket, which is just basically like a folder that's on Google Cloud for the ZTM TensorFlow course under the project Food Vision, which is what we're working with at the moment, and pizza steak. So if the Food 101 dataset has 101 different types of food, you can probably guess how many different types of food the pizza steak dataset has. But that's enough talking about it. Let's see what we might be able to do. Download it. And by the way, this little code here, wget, means get this file and download it into Google Colab here. So let's see this in action. We'll unzip the downloaded file and we'll call this zip ref equals zipfile.zipfile. And then we have to pass it the directory name here, or the document path. There we go. And then we can go zipref.extract all, and then zipref close. Now, we'll shift and enter that. Shouldn't take too long. Wonderful. Took about 3 seconds to download from Google Cloud, and we've got it here. Pizza steak zip saved. And what do we have once we've unzipped it? There we go, pizza steak. There's the zip file, and then we go, pizza steak, test, train. So this is the generic format for data for a computer vision problem, is that you have your overall folder here, and then within it, you have a training file with your training images, and then a test file with your testing images. And the images for your training data, all of these images in the steak folder, you might have guessed, are images of steak. We'll have a look at these later on. And all of these images are images of pizza. And so the reason why we format the data like this is what Image Modification Notebook does. You can find this on the course GitHub, as well as where you find links. That's what that notebook does. It pre-processes our data to be in this format. So with the file, the directory name is the class name of all the images in there. Same with this other class. And the training folder is going, hey, once we write a class going forward, if you look in the training folder and find images of pizza and steak, they're all training set. And if you go into the test folder and find images of pizza and steak, they all belong to the test set. So I'll just copy this link here. Get the data. The images we're working with are from the Food 101 dataset, which is 101 different classes of food, and I'll link that there. However, we've modified it to only use 2 classes, pizza and steak. Now, you might be thinking, why don't we just use all 101? And that is a phenomenal question. It is because, remember, we're serial experimenters. What's a machine learning practitioner's motto? Oh, I don't want that emoji. I want steak. Well, there we go. We've modified it to use only 2 classes using the Image Data Modification Notebook. And I'll just link this here. And while we're linking this, you might be thinking, why do we start small? I'll link this. We'll come back here. Let's put a little key here. We'll answer that question. Okay. This is why we're starting with a smaller data set. We start with a smaller data set so we can experiment quickly and figure out what works, or better yet, what doesn't work before scaling up. Beautiful. So that's what we're doing. We're starting with a small problem, and we're going to gradually increase the complexity as we work towards building our overall application called Food Vision over the next few modules. But now that we've got a data set, that took us a few steps, and oftentimes when you download a data set like this, it might not be as pre-formatted as what we've already done. So that's why I've linked a Image Data Modification Notebook just so you can see how that's done. But now we've got a data set, we can start to inspect the data. So let's see that in the next video. In the last video, we downloaded our dataset, which is a pizzasteak.zip file, and then we unzipped it. So now let's inspect it, which is a very crucial step at the beginning of any machine learning project. So inspect the data. In other words, become one with it. That's what we want to do. We want to build our own internal deep learning model or neural network model in our brain that understands the data before we write any code to understand the data. So let's write this down. A very crucial, I don't say that lightly, crucial step at the beginning of any machine learning project is becoming one with the data. And for a computer vision project, this usually means visualizing many samples of your data. Beautiful. That's all we need to write. Let's start to inspect programmatically what our data looks like. Pizza, steak. Remember, we've downloaded a data file here called pizza steak, pizza_steak, and it's got test and train. So let's start to have a look at what's going on in there. And ls is just basically stands for, well, not basically, it stands for list. So it says list the files in pizza steak, test and train, wonderful. And now we're going to go ls pizza steak, and let's have a look at train. Pizza steak, beautiful, very exciting. And how about inside the steak directory? Pizza, steak, train, steak. There we go. Whoa. Okay. So we've got a whole bunch of different images here. I wonder how many there are. We could write some code to figure that out. We might actually do that. And they've all got different file names. We haven't actually looked at what they look like yet, but we'll get to that. What might we do next? We've got a bunch of images. How many are there? Yeah, let's do that. That's what we said we might do. So import OS, and we might write some code, walk through the pizza steak directory, and list number of files. That's a great idea. So there's a little function in OS called walk. So if we go for dir path, dir names, file names in os.walk, then you pass it the file you want it to walk through. In our case, it's pizza steak. And then we go print f, and then there are, let's go string format, then dir names and directories and len file names, images in, we want dir path. Is that what we're after? So there are length dir names directories and length file names images in dir path. This should work. Let's see what it says. Okay. There are 2 directories and 1 images in pizza steak. What is that? ls pizza steak. That's strange. Files. If we go ls la, can we go like that? Here we go. So usually .ds_store appears in there. So for some reason, when creating this file on my computer, .ds_store has appeared in there, hence why it seems like we've got 1 image in there, but it's actually just ds_store. So we'll ignore that one. But anyway, there are 0 directories and 750 images in pizza steak train. So we've got 750 images of steak for the training set, and 750 images in pizza steak train for pizza. So, okay, 750 images of each, steak and pizza. And then looks like we have 250 images of steak and pizza for testing. So I'll just write a little comment here and go, the extra file in our pizza steak directory is .ds_store. Now, if you're confused at why that's coming up, that is equivalent to that. And same again for the test. Now, let's start to view them, because having a look at this doesn't really look very visual, right? We're working with a computer vision problem, and right now we're just looking at our images in text format. So I think in the next video, we'll start to get a list of our class names programmatically, and then we'll write some, I think we'll use matplotlib to write some code to visualize our photos, our images, so they're not just writing on a screen. Welcome back. In the last video, we saw how we could inspect the directories which are storing our data. Now we're going to write some code to have a look at our images visually, which is a much better way to understand our images. I just want to show you one more way, another way to find out how many images are in a file. Num stake images train. We can set up a variable, and then we can go len os.listdir, which is, so Python is the OS module, and then listdir is a little method to list all of the names in a directory. So we'll give it our pizza steak, maybe train. We'll give it the steak file. So this is going to go, tell me the length of how many files are in the pizza steak directory under the train file in the steak file. So let's go num steak images train. 750. So just a way to sort of directly inspect one directory rather than this one which kind of loops through them all. Let's write some visualization code. I'll write a little note here to visualize our images. First, let's get the class names programmatically. Now, there's actually quite a fair few ways we could visualize images. We could just click on them and just go through them, but whenever possible, I like to write code to inspect stuff. And even within, when we're writing things programmatically, the ways that I'm showing you are only just one way that you could do it. So take them with a grain of salt. These are just ways that I've sort of figured out after working through these problems lots and lots of times. So one way is to get the class names programmatically. If we go here, import pathlib, and import NumPy as NumPy. And I'm going to set up the data dir, which stands for data directory, to be pathlib.path. So I'm going to turn our pizza steak train into a path object, and then I'm going to set up class names equals an NP array of sorted, we want this, item.name for item in datadir.glob star. Wonderful. And so what this is going to do is created a list of class names from the subdirectories. The subdirectories being the subdirectories in the training folder. So if you guess, this is going to come out as print class names ds store. We want to actually get rid of that. So why don't we? I'm going to, we'll just reset this here. So class names equals class names. We will go 1 onwards. Pizza steak. Now, I'm getting it like this. I've got that ds store file in there. By the time you go through this, I'll fix up it to remove ds store, but just remember, if you get .ds store in your class names, you can just remove it like this. So if you need to remove it, you can index on the list. Beautiful. So now I've got our class names, which is pizza and steak. It's time to write some code to visualize an image. Let's visualize our images. So if we want to import matplotlib.pyplot, I'm going to use matplotlib to view our images as plt. Remember, the reason we're doing this is because we're becoming one with the data. We're visualizing, visualizing, visualizing. Whose motto is that? That is the data explorer's motto. If a machine learning practitioner's motto is experiment, 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 the data explorer's motto is visualize, visualize, visualize. Now, I'm a big fan of the power of randomness, and as you get more into deep learning and machine learning, you will also become a big fan of randomness. Target dir, target class. So as you might have guessed, this little function here, view random image, is going to select an image randomly from this path of whatever class that we want. We're going to define the target directory in the target class, and then it's going to plot that image. So let's do that. We will set up the target directory. We'll view images from here. Nice little comment of what's happening. So the target folder equals target dir plus target class. Wonderful. And then we will get a random image path. So that can be random image equals random.sample os.list dir. We want the target folder. And then we want 1. We're using the random module here in Python. We are basically just saying, hey, randomly sample 1 of the items in here. Beautiful. And then we're going to read in the image and plot it using matplotlib. So image equals mp image. So this is this module here, matplot image, mp image.imread. And then we want to pass it the target folder. We want to also give it a slash. That's what I always forget. Don't forget when you're passing something through. If it's got multiple subdirectories, this is where that little slash comes from. Then we want to pass it the random image, and we want to get the 0th index because this is going to be returned back as a list. So we want to just index on that so it comes back as a string. And then, by the way, if you wanted to see what was coming out of this, you could just go print random image, and that'll print out the random image that it's selecting. And we go plot.imshow img. So that's a function in matplotlib's PLT, image show, imshow. So this is going to read it in, and this is going to show it. And then we want to add a title. PLT.title is going to be the target class, so pizza or steak. And then we don't want to see the axes. And finally, we're going to also print the image shape, because that's important to know when we're dealing with any kind of data in deep learning. We want to know its shape, because eventually it's going to be turned into a tensor. And what's one of the most important things with a neural network is lining up the input and output shapes. So let's go show the shape of the image. Return img. All right, so let's step through this. View random image, we pass it a target directory and a target class. We add those together. These are going to be in string format, by the way. We could add a little doc string to tell us that. Then we get a random image path using the random module. And then we use matplotlib as well as matplotlib image to plot that image. Let's see if this works. So we might go view a random image from the training data set. And we want to go img equals view random image. And we put it target dir. Can be, we said the training data set. So we'll go pizza steak train. And then we will go target class equals steak. And let's see what this looks like. Oh no, where did we miss this up? So we're missing, okay, so this is what we get. No such file, directory, pizza steak. So there's somewhere we've messed up. Print random image, target folder. We've given this target folder plus random image, target dir plus target class. Oh, we need a slash here. See, these little errors that you're going to always get. I get these little errors all the time. So let's see what this looks like. Boom, so there's the image number that we've got. There's the image shape, 512, 512, 3. Does that sound familiar to what we've looked at? So 512, 512, is that actually, no it's not, 512 divided by 2 is 256. So previously we've looked at images 224 by 3. But this shape is 512, 512, 3. Let's have a look at another image. Ooh, another image. We could keep going here for a while. So this is the problem with working with different data sets. They may influence to how you feel. After looking at a fair few images of steak, you might get hungry. Okay, let's see if our function also works for pizza. So having a look at what are we trying to look for in these different images? We're trying to figure out, are they different? Is there anything that stands out between them? Is there anything that we should know? And the beautiful thing is we're looking at random samples here. So if there is something wrong, we may not come across it, but because we're looking at so many different random samples, I mean, it's a good idea usually to look at least a dozen or so of each class whenever you're working with a computer vision problem or a binary classification problem, just to get an idea of, okay, are the pizza images, is there anything outlandishly wrong that's going to affect our neural network, so that when it comes to training it later on and evaluating it, if it's getting some crazy results and we know, okay, some of the pizza images are fairly dodgy, we can understand if it doesn't perform too well on those sort of images. Just want to highlight one more thing. You could keep going with this for a while as long as you want, is that the reason why I've returned the IMG value here is because our image, when it's read in by, in our case, we've got MP, IMG, mread, when it's read in, it turns into a big array, which of course is also, we can consider this as a tensor. So if we go image.dtype, uint8, and if we go, what if we try to turn this into a tensor? tf.Constant img. Oh, we don't have TensorFlow. Import TensorFlow as tf. Beautiful. So, how cool is this? This is where it's starting to get really exciting. Things are starting to come together. We are learning how to pre-process images into tensors. And what can we use tensors for? As inputs to our neural network. So if we see here, all of these are different pixel values of red, green, and blue color channels. And this is what equates to a picture like this. Now, do we necessarily need to understand what's going on in this big tensor? No. We much better understand what's going on here. But our neural networks are going to much better understand what's going on in here. So, with that being said, in the next video, let's start to see how we might begin to pre-process it and then figure out how we can start to pre-process this tensor. I'll give you a hint. We've actually looked at this in a previous video. So if you've got an idea of how we might pre-process this, go straight ahead and do that. And then we'll look at how we might build a convolutional neural network to accept this kind of tensor as input. So far we've visualized a fair few of our images. You could keep going if you wanted to get a better idea of them, but we're going to leave that for now. We've seen that when we read our images in, they're actually in the form of a giant array, or a tensor, after we've turned it into a tensor with TensorFlow, of different pixel values. And these are, because there's three color channels, red, green, and blue, are between 0 and 255, which means if this was red, green, blue, and this was 0, and this was 0, and this was 255, this individual pixel here would be a very blue pixel. So we come down, if we wanted to check the shape of our image, so view the image shape, go img.shape. We get here 512 width, 512 height, and 3 different color channels for red, green, and blue. So this is returns width, height, color channels. Now, we could pass this because this is a numerical representation of our image data to a neural network. However, in a previous section, we've discussed it's often important to pre-process our numerical data to get it ready for a neural network. And what was one of the most important steps when pre-processing our numerical data before passing it to a neural network? If you're not sure, that's completely fine. We're going to go back over it. To jog our memories, let's return back to the keynote. We'll go back to the previous slide, jump straight to the end. So we've got our computer vision inputs and outputs. There's a lot going on in this slide, but essentially what we've got is an image. Let's focus on one. Its width is 224, its height is 224, and it's got 3 color channels. We pass it in a numerical encoding form with normalized pixel values. Or scaled. Another word for normalized is scaled. And that's our inputs to a neural network or machine learning algorithm. So we've kind of given it away there, but let's go back to our modeling with TensorFlow. And if we go right to the end, what we're doing now is getting our data ready. So turning it into tensors. Have we turned all our data into numbers? Well, we've got one way to do that with our images. So neural networks can't handle images, they need to be numerical. Make sure you have your tensors the right shape. Well, we haven't quite jumped to that yet, so we're going to skip ahead to scaling features. So normalize or standardize. Neural networks tend to prefer normalization, which is getting all of the values in our input tensor between 0 and 1. Again, another word for normalization is scaling. So how might we do that? So get all the pixel values between 0 and 1. We can just do image.divide by 225. And I do the dot here, so it turns it into a float. And there we go. All of the pixel values are now between 0 and 1. How easy was that? Now, you might be thinking, Daniel, if we had to do that for every image, that would be extremely tedious. And you're completely right. Right now, our viewRandomImage function only views one image at a time. It returns one image. And then if we wanted to pre-process it, to pass it to a neural network, we'd have to write some code to pre-process them all and get the values between 0 and 1. But it's going to take a long time. So you might have guessed, TensorFlow actually provides some functionality to do all of this for us. So that's what we're going to have a look at in the next video. We're going to actually go end to end. If we come back to the keynote, we're going to build the architecture of a CNN. So if we have a look and go through all of these steps, we've got the input layer, the convolutional layer, the hidden activation, the pooling layer, the fully connected layer, the output activation. Whew, this is tiny VGG. So that's what we'll go through in the next video. We'll look at an end-to-end example to both read in data, prepare it for a convolutional neural network. We'll also have a go at coding these layers for the first time. We'll compile our model just like we have before, and then we'll fit it to the data. So I'll see you then. Welcome back. Now I'm super excited for this video. It's going to be a full-on one, but I think you're up to the challenge. We're about to build our first end-to-end convolutional neural network. However, before we jump into that, I just want to put a little tidbit here. I added this to the last video, just continuing off. We put this little key emoji here for write down things that we should note. As we've discussed before, many machine learning models, including neural networks, prefer the values they work with to be between 0 and 1. Knowing this, one of the most common pre-processing steps for working with images is to scale, also referred to as normalize, their pixel values by dividing the image arrays by 255, since 255 is the maximum pixel value. Now, that's just a follow-on from what we did before to finish off that image array, normalizing all of the red, green, and blue pixel values. So without any further ado, let's get into an end-to-end example. Now, as I mentioned before, there will be a few things in this video we haven't quite covered before. However, I'm going to show you the end-to-end example. This is where we're going to end up, and then we're going to work backwards from there. It'll all make sense in a few videos' time. Let's have a look. An end-to-end example. Let's build a convolutional neural network to find patterns in our images. More specifically, we need a way to load our images, pre-process our images to get them into a state like this, because doing this one by one would take far too much time. Pre-process our images, build a CNN to find patterns in our images, and then we need to compile our CNN and then fit the CNN to our training data. So let's do it. What do we start off with? We're going to need TensorFlow, of course. Import TensorFlow as TF. And we're also going to need a new module we haven't quite seen before. Remember, I gave you a warning. There will be a couple of things we haven't quite seen before, but as usual, we're going to step through it by writing code. So image data generator. You may be able to guess what that means. So let's start off how we always do. Set the seed, tf random, set seed 42. And now we're going to set up the data preprocessors. So preprocess data, get all of the pixel values between 0, and 1. This is also called scaling/normalization. Wonderful. And to do this, we're going to set up 2 instances of image data generator. And we're going to pass it a parameter here called rescale. And it's going to be 1 divided by 255. Let's just run this so that we can view the doc string of this. What does it say? Here we go. Generate batches of tensor image data with real-time data augmentation. Now, we haven't covered what data augmentation is, and we haven't really covered what batches of tensor image data is. But we'll see what this looks like in practice, and then we can go through. If you want to go through the documentation before we keep writing the code, feel free to pause this video and come back. But I'd like to encourage you to just continually write code, see what the outputs of your code are, and learn by doing. So now we're going to import data from directories and turn it into batches. We have seen the word batches before, or batch size before, but that's on the keynote. I'm going to finish all this code first before we go back to the keynote. So I'm going to set this up as train data, and I'm going to bring in the instance of image data generator we just created. So train data.flow from directory. You might be able to guess what this does. Now we need to pass it a training. Oh, you know what? We've missed a step. We need to tell TensorFlow set up paths to our data directories. Now, there's a couple of ways we could do this. We could grab this and we could copy the path using that. So for one, we might do that. So this is the training directory of pizza steak. So I'm going to copy path and I'm going to write this down here, train dir equals paste that. This is the same as, we'll go here, test dir equals, you actually don't need this content at the start there. So we can just do it like this as well for the test directory. Wonderful. And then we're going to pass the train dir here. So see what we did? We just took this variable, training directory with all of our training images, and passed it into train data. And this actually needs to be train data gen because we're taking that and putting it here. So this is a flow from directory method. What does this do? Let's view the doc string. Takes a path to a directory and generates batches of augmented data. Now the arguments can be directory. So the first one, directory, that's what we've passed there. We might use the parameter name so we know. Directory equals train dir. Can be a string path to the target directory. Okay, beautiful. And if you keep reading, it's going to say that should contain a bunch of images. There we go. Any PNG, JPEG, or etc. images. And then the next thing we're going to pass in is batch size. So this equals 32. Now I believe by default it is equal to 32. Batch size 32. Batch size 32 is actually very common. You're going to see that a lot in the world of deep learning. But writing code, I will show you something. Google Yarn LeCun batch size, and that's where you'll get 32 from. Target size equals. Now this is the size we want all of our images to be. We saw when we imported one of our images that it was 512 by 512. But for our case, we want to reshape all of the images to be 224 by 224. You might be wondering, why this shape? Well, it's a very common shape to use. It also contains a certain amount of information. Say, a 512 by 512 image may have almost, or will have, over double the amount of information. However, 224 by 224 in practice still withholds a lot of the information within an image. Now again, you can mess around with this size to however you like, but this is a pretty good size for us to work with for now. The class mode we're going to be working with is binary. So that's telling our train data gen that we're importing data in a binary format. We're working with 2 classes. Then finally, we're going to pass seed equals 42 for reproducibility. We've covered a bunch of different parameters there fairly quickly. If you want to have a look into what each of them do, we can kind of deduce what they do from reading them here. But don't forget, you can read the documentation for this. We're going to keep going. You might have guessed, we also need to set up one for the test data, but this is going to be a little bit confusing. I'm calling it valid data, but that'll be clear in a moment as well. And we're going to go valid data gen dot, this is coming from up here by the way, valid data gen dot flow from directory. You might have guessed we're going to pass in this directory. This is going to be the tester. The batch size is going to be 32. The target size, what shape do we want our images to load in? It's going to be the exact same as the training images. Same thing for class mode. It's going to be binary. And then the seed is going to equal 42. Wonderful. So what have we done so far? We've loaded our images. We've pre-processed our images using the image data generator class. Now we're going to build a CNN to find patterns in our images. Whew. We are covering a lot. So build a CNN model, and this is the same as tiny VGG on the CNN Explainer website. If you want to skip ahead, you can Google the CNN Explainer website and check that out. We're actually going to have a look at that in a moment, but I'm just going to write the code to replicate the model on the CNN Explainer website, which is the tiny VGG convolutional neural network architecture, which might not mean much to you for now, but we will see what it looks like in practice. So I'm going to set up a Keras sequential model, and then the first layer is going to be tf Keras layers conv 2D. The first parameter I'm going to pass here is filters. There will be 10. Then the kernel size. Again, we've covered none of these, but we're going to see them soon. I just want you to get hands-on writing your first convolutional neural network as fast as possible. Activation equals ReLU. Then we're going to set up the input shape. Now, this is the input shape our first layer is going to take. It's going to take images in the form of 224 by 224 by 3. So that's what this pre-processing function is going to do. Reshape our images into 224, 224, and then also the 3 is going to be for color channels. So that's where that comes from. And now we're going to go into another layer. Let's have one of the exact same. So this is going to be tf Keras layers conv 2D, except this time we're not going to pass it any parameters. It's just going to be 10, 3, and then activation equals ReLU. Wonderful. This layer here is actually the exact same as this layer. If we look at the doc string here, it goes filters, kernel size, strides, the default is 1.1. Again, you're going to read all these and go, whoa, what is going on here, Daniel? We're writing convolutional neural networks from scratch. And we go, oh, actually, not really from scratch. We're using TensorFlow to do so. MatMul 2D. This is coming directly from colored block addition. Pool size equals 2, and the padding here is going to equal valid. We haven't seen the MatMul 2D layer, but that's okay. And now the tiny VGG architecture actually has 2 more convolutional layers. tf Keras layers conv 2D, 10, 3, activation equals ReLU. Oh, we've been using double apostrophes, so I'm going to keep it that way. ReLU. And then it's going to have another convolutional layer, layers conv 2D. And then we're going to go 10, 3, activation equals ReLU. Wonderful. And then we're going to have another MatMul. So tf Keras layers dot MatMul 2D. You see the pattern we're sort of building up here? We can pass it 2 there. We've got 2 conv layers, then a MatMul layer. 2 conv layers, then a MatMul layer. Now we're going to have tf Keras layers flatten of the MatMul layer before we pass it to the output layer, tf Keras dot layers dot dense 1, because we're using binary classification. Activation function is going to be sigmoid. Boom. Look at that. This is our first ever CNN model. I'm so excited, and I do know we did cover this very fast, but don't you worry. If you want to jump ahead and see what's going on here, I highly encourage you to search up the CNN Explainer website. But as I said, we're not leaving this Google Colab until we've built an end-to-end example. So this is our model. Now what do we do once we've built a model? Come up here. We've built CNN to find patterns in our images. Now we have to compile our CNN. So let's do that. Now this is something we've had practice with. Compile our CNN. I want you to have a think about it. What might our loss function be if we're doing a binary classification problem? What might our optimizer be? And if we're doing a classification problem, what's a good metric to begin with? So you might have already gone ahead and compiled our model, but if not, that's okay. Let's do it together. We're going to use binary cross entropy as a loss function because we're working with a binary classification problem. And let's set up our optimizer to be tf.Keras optimizers.atom. Wonderful. And then we're going to set up the metrics. Now, because we're working in classification, accuracy is a good metric to start with. And then we're going to fit the model, history1 equals model1.fit. What do you think we can pass in here? If we came up here, where's our training data? Here we've got it. We've got it in a training data object. We've got validation data here too. So what we can do with the fit function is pass train data directly to that. And because train data is an image data generator class of the training directory, already pre-processed for us. So we can pass that straight to our neural network. Then we're going to fit it for 5 epochs. The beautiful thing about this class actually, flow from directory, is that it creates the data and labels automatically for us. So that's why we can pass it here, train data, without having to pass X and Y to .fit. The labels and data get created for us in this train data object. Then we can go epochs 5. We're going to introduce ourselves to another parameter here, which is steps per epoch. Steps per epoch is going to be len train data. So if we have a look at the length of our training data, oh, we can't see it there. I'm going to just comment this out, run this cell. There we go. So this is what outputs when we run these. It has found 1,500 images belonging to 2 classes and 500 images belonging to 2 classes. So this is the training data, 750 images per class, and this is the testing data, 250 images per class. And if we go len training data, 47. Now you might be wondering where that came from, but if we go 1,500 divided by 32, because we've got a batch size of 32, what does that equal? 46.875. So now we have 47 batches of 32 images and their labels because there's 1,500 total images. Now the reason we put things into batches is because that way it can all fit in memory of our computer chip. So if we tried to calculate the patterns on all images in one hit, our computer might run out of memory. But if we merge them or if we splice them into batches, it gives our computer a chance to calculate the patterns on the first 32 images, then the second 32, the third 32, and so on, to work out the patterns for the overall entire image data set. So if we come in here, that's why we wanted to go steps per epoch. We needed to do 47 steps per epoch. So 47 passes across the data, 1 for each batch. And then the validation data is going to be equal to the valid data. And then the validation steps, which is the same thing as steps per epoch, is going to be len valid data. Far out. Did we just cover a lot of ground or what? But I'm so excited because we're about to look at this all in one cell. This is what we've done. We've loaded our images, we've pre-processed our images, we've built a CNN to find patterns in our images, we've compiled our CNN. Now it's time to fit it to our training data. Do you reckon we've made a mistake? Are you ready to run it with me? I'll give you a second to catch up. If you need to write some code, that's okay. Finish writing out what's in this cell. I'll scroll up a little bit so you can see what's going on, but we're about to run it in 3, 2, 1. Your first convolutional neural network built by yourself. Or if you've done deep learning before, this might be another one, but the first one we've built together in this course, look at this. Oh my gosh, this is beautiful. It's fitting on the data. Epoch 1 of 5. Now we've got a fairly large ETA here. This is probably the longest ETA we've had to wait for. This is over a minute. What's going on here? Why is this taking so long? I might give you a guess. Why do you think this ETA is taking so long? I'll give you, it's nothing to do with the code we've written. It's actually to do with the runtime we're running. You see here, we're not using any kind of hardware acceleration. So we're trying to calculate all the patterns on our data without a GPU. So that's probably what we'll do in the next video, is we'll change our hardware to a GPU. I'll let this run for about 1 epoch, and you can do the same. You can actually let it run the whole time if you've got the patience to. But I'm going to stop mine after 1 epoch, and I'm going to come back in the next video and compare and see how much faster it runs with a GPU versus without a GPU, which is what we're doing now, running without a GPU. So let yours run for a little bit, at least 1 epoch, so you can see how long it goes for 1 epoch. And I'll see you in the next video, and we'll speed up this code. Welcome back. So in the last video, we covered a fair bit of ground. And I know we went through a lot, but that's okay. We're going to slowly break it all down over the next few videos. I just wanted to show you what we're working towards. We've got a full end-to-end example here in one cell. And we kind of cut our, well, I did. I'm not sure if you waited for it to fit, but I cut my neural network short. So it only got about a third of the way through its second epoch because it was taking 91 seconds per epoch. And we found out that it was probably taking that long because we're not using GPU acceleration. So what I'm going to do here is just to exemplify the power of a GPU and the beautiful thing about Google Colab offering us the use of one for free. I'm just going to put this here and comment it out just so we know it took 91 seconds for the first epoch. And usually, this is another just little tidbit while it's on the top of my head, is whenever you're running a neural network that's going to load images or load some kind of data, usually the first epoch is about 50% longer, give or take some arbitrary amount. So the first epoch is usually a fairly significantly amount of time longer than the other epochs because it has to load all of the data into memory. But then subsequent epochs, as we'll see in a second, are usually quite faster than the first one. So that's just a heads up for going forward. Now, let's improve the speed of this by going runtime, change runtime type, GPU. I'm going to save. Now, what we're going to have to do, we might have to rerun some cells above because when you change the runtime type, it actually resets all of the saved variables that you have. But let's just see if we can run this cell. All we've done is change from not using a GPU to using a GPU. Shift and enter. No such file or directory. Did it delete all of our files? It did. So that's what we're going to have to do. We're going to have to come back up here to get the data. And we're going to have to re-download the data here. We press Shift and enter. Luckily we've set up this code cell before. Shouldn't take too long. Do we have it there? We do. Beautiful. And so now we can just go back. We'll go back to our end-to-end example. And we're going to run this cell. Hopefully that's the only cell we need to run. All right, found 1,500 images belonging to 2 classes. It's the training data. This is the testing data, 500 images. Epoch 1 of 5. What's our time to beat? This is a time trial for the Google Colab GPU-powered instance. We had 91 seconds. Oh my goodness. Look at this. This is just a powerhouse already. How long was that? About 10? 17 seconds. So, wow. We might actually do all 5 epochs in the time it took us to do 1, just by giving ourselves a GPU to use. We can even just sit here and talk. This is one of my most favorite activities in the world, actually, is just watching a neural network train. And it's even better when the metrics are coming out pretty good. Like, look at the performance on the training data. Remember, the neural network we're building here is to classify whether an image is of pizza or of steak. So right now it started at 64% accuracy, finished at 85.5% accuracy on the training data set, and finished at close to 90% accuracy on the validation data set. How cool is that? And all of it, what's that? 17 plus 9, 26 plus 9, 35 plus 9, 44 plus 9, 53 seconds. So almost half the time to train 5 epochs as it took to train 1 epoch by just switching to GPUs. So I'm going to put a little note there. This is just for you going forward. Note, if the above cell is taking longer than 10 seconds per epoch, make sure you're using a GPU by going to runtime, change runtime type, and then hardware accelerator GPU. You may have to rerun some cells above. Beautiful. Alrighty, and you see what I mean by the first epoch taking almost double the amount of time as the subsequent epochs? That's just because it was loading data into memory to be able to run and find patterns on. And clearly our network is doing pretty well. And speaking of doing pretty well, I want to let you in on a little secret of what we've just done. So if we search data vision food 101, it should come up. Does it come up with the original? Here we go. This is the original food 101 paper. Scientific paper. So food 101, mining discriminative components with random forests. So this paper was published, I believe it was 2014. There may be a date here, you can correct me if I'm wrong, but let's just say it's 2014. They used a random forest algorithm. What we just used was a convolutional neural network. So actually, convolutional neural networks have been around for a few decades now, but they've only sort of recently in the last, say, 10 years or so, become really prevalent and accessible to people like you and me. But what we've done is, where's the results here? So they, on 101 food categories with 101,000 images, had an average accuracy of 50.76%. Wow. Okay, across 101 class food categories. Now, if we go back, and it even says their model outperforms alternative classification methods except for CNN. Oh, what have we done? We've used a CNN. So if we look at this, 50.76% accuracy. This is across 101 food categories though. But with our 10-line convolutional neural network, we've just got 88% accuracy. But again, theirs was on 101 classes. Ours was only on 2 classes, but that's just giving you some sort of insight into the power of a convolutional neural network. Now, before we finish this lecture, I said in one of the previous videos that this architecture that we've got here is a CNN model based on the tiny VGG on the CNN Explainer website. So this is going to be your homework for this video. I'm going to write this down here. First of all, we're going to get a model summary. We're going to go model1.summary and have a look at it here. We can inspect it there. There's the input layer, all these different parameters here. Total params, 31,101. But I want you to pay attention to the layers we've built. conv2d, maxpool, conv2d, conv2d. Well, this is a bit of a tongue twister. Maxpool, flatten, dense. So pay particular attention to this. And now we'll go through the CNN, or actually this is your homework, so you're going to go through the CNN Explainer website. Now this is one of my favorite resources of all time on convolutional neural networks. So I want you to just have a play around with this for at least 10 minutes. Again, there's probably a lot of stuff here that you haven't seen before, but that's okay. Check out the layers of this neural network here and how does that compare to our own. Step through all of these images here and have a read. Might take a little bit longer than 10 minutes, but I'd like you to read through this entire page because this is going to be in the extra curriculum as well. But this is probably the best explanation, or one of the best, because there's many great ones out there, of what happens in a convolutional neural network on the entire internet. So have a play around with that. That's your homework for this video. And the question is, how does this network relate to the one that we've just created? We've kind of given away the answer, but I want you to make the connection yourself. So I'll leave this link here. I'll write down here. This is going to be practice/exercise. Go through the CNN Explainer website for a minimum of 10 minutes and compare our neural network with theirs. Turn that into Markdown. Of course, this will be in the practice/exercise/extracurriculum section as well, but I'd like you to go through that before we push forward with convolutional neural networks. I'll see you in the next video. How did you go? Did you go through the CNN Explainer website? Did you figure out what the commonalities are between, or commonality is between, the model that we built and the model that's running across here? We've got an input, a conv layer, relu, conv, relu, maxpool, conv, relu, conv, relu. Where have we seen that before? Well, I'll give you a hint. We replicated it here. Now, where they've got relu here, what we've done is we've just included it within our convolutional layer. So we've just set the activation here. If you really wanted to, you could also set it up as, where can we put it? We could put one here, tf.Keras. This is how you might add an activation just on top. Activations, tf.nn.relu. So that would be the same as this. So if we remove that, we've just got the exact same setup that we had before, but now we've just added in an extra layer. So I'll move that there. The trade-offs of that won't seem very clear now, but if you do need to separate your activation functions from your individual layers, you can always put them as their own layer. So just keep that in mind going forward. But that's all the difference is there. But otherwise, how exciting is that? You've already replicated a neural network that you found in the wild. And speaking of neural networks that we found in the wild, how about we see, just to demonstrate the versatility of neural networks in general, how about we see how the same model that we've built before goes on our different data set? Yeah, that sounds like a good idea. So in this video, we're going to see how we can use the same model as before. More specifically, the model we built with the TensorFlow playground, playground.tensorflow.org. Is it .com or .org? We're about to find out, aren't we? There we go. Wonderful. So we can tinker with a neural network right here in your browser. Remember in a previous video, we built a neural network with 2 hidden layers and 4 neurons per layer. And then we made sure we had ReLU activation. We changed the learning rate. What was it? Atom. Trusty learning rate of Atom is 0.001. And we had classification. But that neural network only worked with dots. Now we're working with a little bit more of a complex data set. We've got images of pizza and images of steak. But let's replicate. I'm going to have some more practice building neural networks. Let's replicate this model to see if it works with our image data set. How might we do that? So let's go here. Let's go set random seed. And then we'll put a little note here. Let's replicate the model we've built in a previous section to see if it works with our image data. And the model we're building is from the TensorFlow playground. So I believe we can just copy this here. This is a beautiful thing about the TensorFlow playground. That's a really long link. I'm actually going to get rid of that. And then I'm just going to turn this into a link. Wonderful. There we go. That should link to that model. So we'll set the random seed, tf random.setSeed. This is going to be an awesome test to see, first of all, compare the convolutional neural network to another style of model. Create a model to replicate the TensorFlow playground model, and also be a good experiment to check the diversity of neural networks in general. We'll come back over here. Now we've got a little bit of practice building these dense neural networks. If I could get my cursor to the start of the line, tf.Keras.layers. The first one we're going to need is flatten, because we need to reshape, or at least tell our neural network that the input shape of our data is actually now 224, 2243, because that's what our images are in. Remember, in our train data object, we can have a look here. Train data. There we go. Directory iterator. And then we can build our 2-layer neural network. tf.Keras layers dense. Dense, there we go. For activation can be ReLU. And we'll go in here, tf.Keras.layers.dense. 4, and the activation is relu. Wonderful. And then tf.layers dense 1 activation equals sigmoid. Now, how do we compile the model? So the beautiful thing about this is that we can just use the exact same compile parameters as above, equals binary cross entropy. Beautiful. And the optimizer is going to be tf optimizers. Yes, that's a correct typing, not my own typing. Metrics equals accuracy. Beautiful. And then, of course, we're going to fit the model. We'll save it to history 2 equals model 2. Oh, getting ahead of myself there. Model 3, train data, because then we can pass it just the train data block that we've created before. And the epochs is going to be for 5, just the same as what we've done for our convolutional neural network. Steps per epoch equals len train data. And then we'll go validation data equals, so we want the validation data parameter here, as you might have seen, just gives our model a chance to train and validate itself at the exact same time. Validation steps, kind of like calling model.evaluate as training is happening. Beautiful. Now, are you ready for this? Is it going to work? Will our neural network, our new one, same one we've built before in a previous video, work with images? There's only one way to find out. If in doubt, run the code. All right, fingers crossed. Wow! This is going really fast. Because you know why? We've switched to a GPU hardware accelerator, and our data is already loaded, so it's just flying through these epochs. But its performance isn't doing too well compared to our convolutional neural network. Like, look at this. It's basically guessing on the validation data. And the training data is not doing too well either. But the good news is that we're failing fast here. At the end of the day, because our experiment is small, we've reduced our training data to only 2 classes, and we're only fitting for 5 epochs. That's only 40 seconds or so that we know, okay, something's wrong here. Our neural network, model 2, the same neural network that we've used in a previous video, isn't quite working with our image data. Now, I want you to have a think about how might we upgrade this model, or something else. Maybe we fit for longer, but I'll give you a little nudge here. Do you think fitting for longer is going to really help? Val accuracy has basically been a coin toss the whole time. So, I'll give you a hint. We need to change this architecture in some way, shape, or form. Do we add more layers? Do we increase the number of hidden units? I'll leave you to think about that until the next video, and what we'll do is we're going to upgrade this model to see if it can find patterns in our image data. But before we do go to that next video, I'd like you to give it a try. So take this, create model 3, and upgrade it in some way, shape, or form so that it finds, we actually beat the validation accuracy of model 2. Because a coin toss is, let's just say that's not going to cut it. So, give that a shot, and I'll see you in the next video. How'd you go? Were you able to create Model 3? Did it perform better than Model 2? I surely hope so, because Model 2's performance was absolutely atrocious. But before we create Model 3, let's get a summary of Model 2. Oh, I didn't even type any code there. Come on, Daniel. Model 2.summary. All right. Holy bejeebers. 602 trainable parameters. Why does that number ring a bell? Well, it doesn't really. It's just a lot higher than our convolutional neural network. So our convolutional neural network had a total parameter count of 31,101, and they were all trainable, whereas our dense model, fully connected layers, had 602,000, or just over 602,000 total parameters. So despite having 20 times more parameters, than our first model, Model 2 still performs terribly. What's going on here? Is this giving us a little hint to the power of convolutional neural networks? Well, let's not stop there. If you're wondering what parameters are, or trainable parameters, well, these are learnable patterns that the model can figure out during training. That's how you think about them. So there's a big weights matrix, and these are all numbers of individual numbers in that big weights matrix, aka patterns that a model learns when it starts to look at training data. But let's try to improve this Model 2. So let's write down here, despite having 20x more parameters than our CNN Model 1, Model 2 performs terribly. Let's try to improve it. Now, I hope you did have a go at improving it. Some ways that we can improve our models is add layers or increase the hidden units. So why don't we do that? We'll add an extra layer and we'll increase the hidden units and see if Model 3 goes a little bit better. So we'll start off, set the random seed, tf random set seed for reproducible results, and then we'll go create the model, same as above, but let's step it up a notch. Oh yeah. Model 3 equals tf.Keras.sequential. Beautiful. We're coming over here, tf.Keras layers. I think we'll add an extra layer. So the previous one had 2 layers. This is going to have 3. And the previous one had 4 hidden units per layer. This one's going to have 100. So we're increasing the number of hidden units by 25 times per layer. Activation can be relu, tf.Keras.layers.dense. We could really just copy and paste this, but we're following our rule. If in doubt, write the code. If in doubt, run the code. And then we're going to go here. tf.Keras layers dense 100, and activation is our faithful relu. Beautiful. And then we need an output layer, which is going to be the exact same as above. tf.Keras, no, tf.Keras, tf.Keras.Keras. Don't pay attention to what I'm writing as I'm writing it. Only copy the finished product. There we go. Okay. Or write it for yourself. Now, compile the model. Your model ability, writing ability, is probably better than mine by now. Because we've written so many gosh darn models. Loss equals binary cross entropy. What did I say at the start? We were going to write a lot of models. And then we're going to go optimizer equals tf.Keras.optimizers.atom. Beautiful. And then we're going to set up our metrics just to be accuracy. This is the same as, we haven't actually changed the compilation across all 3 models. And then we're going to fit the model. So we need history 3 equals model 3.fit. Tesla have a car called the Model 3. It's a great car. I see a couple of red ones and I think a grey one driving around my home city. Steps per epoch equals len train data. And you know what they use? They use computer vision. And you know what we're writing? We're writing computer vision code. Albeit our dense model isn't performing as well as our CNN model. Validation data. Validation steps equals len valid data. Beautiful. All right. Do we think, so Model 2 performed like trash, basically a coin toss in our binary classification problem. But we've upgraded Model 3, we've added a dense layer, and we've increased the hidden unit size by 100. Oh, sorry, by 25 times to 100. So from 4 to 100. Let's run this and see what happens. Oh my goodness, what do we get wrong? Do we need a flatten layer? Yes, we do. That's what we need to do. We need to flatten our image tensors as they come in. Layers.flatten input shape. But why does this error give us anything away? Logits and labels must have same shape. So yeah, whenever you see a value error that says something about shape, there is 100%, or not 100% because nothing's ever certain, but there's most likely some sort of shape mismatch with your model somewhere. So remember, in a deep learning model, each layer's output is a subsequent layer's input. So if we have a dense layer here as our first layer, we didn't have this flattened layer here before, it's expecting things in a certain input shape. So we need to flatten our images as we pass it in. This should work. Fingers crossed. Beautiful. There we go. Okay. Now this is still operating nice and fast. That's what we want. We're all about speed here. Oh, yes. Validation accuracy, 68%. We've already seen an improvement. And again, this is only taking about 8 seconds, 9 seconds per epoch. So we can probably sit here and chat to each other while it trains. That's one of the problems you're going to have actually as you get further and further into deep learning, is figuring out what you should do while your model trains. I actually like to do push-ups or go for a walk, just because sitting at a computer for too long, you know, not great for the posture. Oh my goodness, maybe that's a future course. Posture for machine learning engineers. Look at that. 74%. That is much better than our scumbag Model 2, but still nowhere near as good as our convolutional neural network at performing close to 89% accuracy on the validation dataset. And I want to show you something. Get a summary of Model 3. Model 3.summary. This is going to really exemplify the power of convolutional neural networks. So this Model 3 did okay on that dataset. We've got to give it to it. It did okay. It did better than guessing, not as good as our convolutional neural network. However, we can't let it off the hook with this. Look at that. 15 million, over 15 million trainable parameters. So not only did it have, I think it's 500 times. What did our convolutional neural network have? 15 million divided by 31,000. Is that going to work? No, it doesn't take commas. Oops. 500 times? Or close to 500 times. So Model 3 has almost 500 times the parameters of our convolutional neural network. Come back up here. Here we go. Total parameters. This is our convolutional neural network. But still doesn't perform anywhere near as good. That is a prime example of the power of convolutional neural networks. So with that being said, I hope now that you understand how powerful convolutional neural networks are, especially for things like computer vision. But I hope you also understand is that deep learning models are actually quite versatile. Or neural networks in general. So depending on how you format your data, as long as it's in some kind of tensor, chances are you can build almost any neural network you want with TensorFlow. And I mean, if there are patterns there, the neural network will probably find them. It just depends on what kind of problem you're working with will dictate what kind of model you should use. And generally with computer vision, you use convolutional neural networks. So with that being said, what did we do before? We did an end-to-end example, but we burned through it really quickly. So what we're going to do over the next few videos is break this down and see what's actually happening in each one of these. And so for the meantime, before we get into what's actually going on in this convolutional neural network model, you've got another bit of homework, and that's to go back through the CNN Explainer website and read through this. I'm going to read through it as well, so I'm going to be talking to it as well. It's a phenomenal, phenomenal resource. So just read it end to end, even if you don't understand something, and have a play around with this graphic, because that's going to come through in a later video. So I'll play around with it too, and we'll discuss this in a future video. So with that being said, take a break, enjoy yourself, and I'll see you soon. Welcome back. Before we kick off this video, I just want to let you know here that I've added a little key and a note before to follow on from what we were talking about in the last few videos about the number of parameters. So you can think of trainable parameters as patterns a model can learn from data. Now, intuitively, you might think there is more is better. As we saw here, our dense neural network, or Model 3, had 15 million trainable parameters, but it had 500 times the amount of parameters in our convolutional neural network. And in lots of cases, having more parameters is better. But in this case, our case, the difference here is that the two different styles of model that we're using. Oh, there's another typo. Finding all these typos here. So where a series of dense layers has a number of different learnable parameters connected to each other, and hence a higher number of possible learnable parameters, A convolutional neural network seeks to sort out and learn the most important patterns in an image. So even though there are less learnable parameters in our convolutional neural network, which is model 1, so if we go model 1.summary, we'll check this out. Boom. We have 31,000 trainable parameters. So even though there are less learnable parameters in our convolutional neural network, these are often more helpful in deciphering between different features. Remember, a feature in an image can be almost anything you can imagine, but we actually don't define those features. So a convolutional neural network might learn an important feature of a picture of pizza is that it's round around the edges. So convolutional neural networks are better usually at deciphering features in visual data than dense networks. But as you saw, we can also use dense networks or dense layers to still get a result on our image data. It just wasn't as good. So with that being said, let's jump back to our end-to-end example. We saw this a couple of videos ago, and we did cover a lot, right? We loaded the images, pre-processed the images, built a CNN, compiled the CNN, and fit the CNN. So we really did breeze through all of these steps. So over the next series of videos, what we're going to do is break all of these down, particularly what's going on here when we build a CNN model. So with that being said, let's come down to where we were before. We'll get started. So I'm going to write this down. Binary classification. Let's break it down. Wonderful. And we really went through about 7 different steps here. Become one with the data. Remember our motto. The Data Explorer's motto is visualize, visualize, visualize. Should do that with every new data set that you're working with. Then we pre-process the data. So we prepared it for our model. The main step here was scaling / normalizing. And then number 3, we created a model. And it's usually good with any neural network problem or any model building experiment session is to start with a baseline. In our case, the baseline was the Food 101 original paper. We wanted to try and beat that. That's usually a good way when you're working with deep learning, is to have some sort of paper or some sort of benchmark and try to create a model that beats that benchmark. If a benchmark doesn't exist, you can create one yourself. Then we fit the model. Number 5 is we evaluate the model. And number 6 is we adjust different parameters and improve the model. Here's where we try to beat our baseline. Remember, machine learning and deep learning is very experimental. So experiment, experiment, experiment. And that's this step. Repeat until satisfied. Experiment, experiment, experiment. So what we're going to do is we're going to break each of these down. So number 1, let's become one with the data again. So what did we do? We created a function before to visualize data. What I might do actually is also make another heading here. 1, become one with the data. Just so we can break it down. And also in Google Colab, that also makes it a nice little It'd be good if they had the number there, but they don't. That's all right. Visualize that. Might be an update to Google Colab in the future to have that. So we're going to create a plot. We'll create a subplot because we're working with binary classification. Remember, our data set is pizza and steak. And we'll get a steak image. We can do that by using our view random image function. And then we pass it the path to our steak training data. Or it could be, I'm going to visualize the training images rather than the testing images. We'll pass it that, because then see there, if we go get we really should have wrote a docstring for this function so we could get some information on it for ourselves later on. But we just had the target directory there. In our case, I've used the training directory. And the target class is steak. And then we can create pizza image equals just the same as above. But we're going to change it to pizza steak train. And we'll view one of our training images. Again, this is going to just visualize. Well, let's just run the code, actually. That's a better way of explaining it. Wonderful. So there's the file path for our steak image. This could be a little bit prettier, but that's all right. We get the point. The image shape of our steak is 384 512. This is important to remember here. So this is the shape of the array or the tensor that our image gets read into. And if you recall back to our end-to-end example, we reshaped our images to all be the same size. And the image shape here is, this is a pizza. So obviously it's a lot higher. So this, I believe, is height, width, color channels. Then if we do it again, we see steak and some pizza. Oh, that's an interesting looking pizza. So this is where it's helpful to become one with the data, right? We visualize, we could do this, ideally you could do this for as long as you want, depending on what data set you're working with, depending on how many classes you have, depending on what you're looking for. See, we're working with a relatively simple binary classification problem, and our data is pretty distinct from each other. But if you had a more complicated data set, you might want to spend a little bit more time than what we're doing, getting familiar with it and becoming one with the data. And I'm a real big fan of viewing random samples of your data set rather than sort of just picking them and choosing them. Wonderful. Okay, so getting pretty familiar with what's going on here. Oh, this is quite... Do you see how this shape here is very similar to what's going on here? So that's an interesting one. That may be an instance where our model gets a little bit confused with what's going on. Because see here, we've got some very similar shape, very similar color in these two. But again, when we discussed that a convolutional neural network is going to learn features of an image, we visualize another one. So a feature of pizza might be that it has some sort of distinct edges. That could be the slicing. A steak, I mean, who knows what it's going to learn. This is the beauty of neural networks, is that it figures out the things that it has to learn itself. Can you imagine trying to hand code some sort of program to go, okay, if you see an image and it's got darkness around some sort of edge, well then it probably is a steak. And if you see an image and it's got some red mixed in with some yellowy color, then it's probably a pizza because that's sauce and cheese. I mean, there's too much going on. And this is only in 2 different classes. All right, we've visualized enough images. So what we're going to have to do next is, what's step number 2? Become one with the data. And again, our data set, we've actually downloaded this in a previous video, has already been formatted for us into this sort of standardized way. There is a notebook in the TensorFlow deep learning repo if you want to see how that was pre-processed there. Image data modification. So this notebook just goes through a few steps of how you can pre-process your images to be in a format like this. So that was becoming one with the data. Visualize, visualize, visualize. In the next video, we'll go over step number 2, which is pre-process the data. We'll see how we can do that. Welcome back. So in the last video, we became one with the data. We visualized a bunch of random samples, checked out our steak and pizza classes. Now it's time to prepare our data to be used with a model. And this is, I'm not just pulling these out of the air, by the way. These are actual steps within steps with modeling with TensorFlow. Like, look at this beautiful graphic. You're gonna not pay attention to this beautiful graphic? So we're up to here. And I mean, I know these steps are a little bit different to the ones we're going through right now, but we still have to get our data ready. And this is what we're gonna take care of here, is turn all data into numbers. Neural networks can't handle images directly. We need to make sure all of our tensors are the right shape, and we're going to scale our features. So normalize or standardize. Neural networks tend to prefer normalization, again, also referred to as scaling, getting the values between 0 and 1. Let's go back to our keynote. We're going to put a little heading here. You want to go be pre-process the data. Prepare it for a model. Wonderful. And so one of the most important steps for a machine learning project is to split data into a training and test set. So we come to our files. Luckily, that's already done for us. We could create a validation set, but for now, we're just going to leave it at training and test. Beautiful. Now that that's done for us, let's define our directory dataset paths. So we have a train dir is going to be pizza underscore steak train, and the test dir is pizza underscore steak test. Now, of course, depending on where your data is stored, if it's even called pizza or steak, you might want to change this. But in our case, this is our training directory, and this is our testing directory. So we'll go there. Now I'm going to write this one down, and that's our next step is to turn our data into batches. Now, we have spoken of this concept of batches in the past, but we haven't quite exactly seen it. I'll just give you a quick definition. A batch is a small subset of the data set that a model looks at during training. So rather than looking at all 10,000 examples at one time, or 10,000 images at one time, and trying to find patterns, a model might only look at 32 images at a time. So I'll write this down. So a batch is a small subset of data. Rather than look at all 10,000 images. Remember, 10,000, this is just an arbitrary number. I think we're working with about 1,500 training images, so you could insert that if you want. At one time, a model might only look at 32 at a time. Now, it does this for a couple of reasons. Number one is 10,000 images, or however many you have. You might have 1,000,000 images. So 1,000,000 images, 10,000 images or more, potentially 1,000,000, or even more than 1,000,000, might not fit into the memory of your processor, GPU. In our case, Colab has been so kind to lend us a GPU. We can check out which one we're using by running NVIDIA SMI. So we have a Tesla T4, which is a pretty darn powerful GPU. It's got close to 16 gigabytes of memory, so that's actually a fair bit. But remember, we have to fit in our models, patterns, and whatnot, and all different things in there. So who knows how many images it can hold at one time, but it certainly can't hold 1,000,000 images, so that's why we look at 32 at a time. And trying to learn the patterns in 10,000 images in one hit could result in the model not being able to learn very well. So what it does, it'll look at 10,000 or 32 images at a time and then calculate how it can improve on that 32, and then another section of 32, and then another section of 32 until it's through all of the training data, and then add it all up, and that'd be one epoch. And now you might be asking, why 32? And I'm going to say, because 32 is good for your health. You're like, Daniel, are you a madman? 32 is good for your health? Is this like 42 being the answer to the universe? Well, no. If we Google Jan LeCun batch size, Jan LeCun on Twitter, now we'll zoom in here. Training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends don't let friends use mini batches larger than 32. Wow, okay. Thank you for that vital piece of information, Jan. You might be wondering, well, who's Jan LeCun? Well, Jan LeCun is the founder of convolutional neural networks, and he's also a professor at NYU, chief AI scientist at Facebook, researcher in AI, machine learning, and ACM Turing Award laureate. Far out. The deeper you get into deep learning, the more you're going to learn about Jan LeCun, one of the pioneers of the field. Anyway, of course, 32, that tweet you can consider a little bit of a meme, but it actually does hold some truth, because 32 is actually possibly the most commonly used default value in many deep learning libraries. But then again, of course, like many different hyperparameters in deep learning, you can change it to suit your needs. But for the majority of what we're going to be working with, we're going to use a batch size of 32. Whew. Now that was a fair bit of explanation. Let's get back to writing code. So the first thing we're going to do to start turning our data into batches and pre-processing it for our convolutional neural network is we're going to create, train, and test data generators and rescale the data. This is another important concept you'll often come across in many deep learning libraries, including, especially TensorFlow, is efficient ways to load your data into memory so that a neural network can find patterns into it. In it, or into it. Anyway, you know what I'm talking about. So what we're going to do is go from TensorFlow.keras.preprocessing.image import image data generator, And then we're going to go train underscore data gen. We'll have a look at what the image data generator class is in a second. I just want to finish writing this code before we jump around to somewhere else. 255. And then test data gen is going to be image data generator rescale equals 1 divided by 2.255. So that rescale parameter here is basically saying when you load our images, divide all of the pixel values by 255. Because if you remember what we did back up here when we inspected our data, we loaded in an image array and it came in values like this, red, green, blue pixel values of between 0 and 255. However, we wanted them between 0 and 1. So that's why we divided them by 255 with a decimal, so it turned it into a float. Let's go back down to where we were. You might be able to hear, I'm not sure. I think my MacBook is telling me I'm using too much processing power, so there's a slight fan in the background. I apologize, but I'm sure you'll be able to hear my voice over that. Let's check out the documentation for image data generator. Of course, we could look at the doc string by pressing Shift Command Space. There's a few. I often find this a little bit hard to read. I'll often scroll through it and try to find one little thing, but usually I just look up TensorFlow image data generator. Then we come in here. There we go. Image data generator. I find this a little bit easy to read. Whoa! We find there's a lot of different parameters that we can pass to the image data generator. So we won't go through all of these. We're just going to go through some of the most important ones that we're going to actually be using. If you want to go through each and every one of them, you can go through the documentation here. But if you see this rescale parameter, that's the one that we've used. So if we come down, find it here, the rescaling factor defaults to none. If none or 0, no rescaling is applied. Otherwise, we multiply the data by the value provided. After applying all other transformations, you might be thinking, what are all these other transformations? Well, we've got vertical flip, horizontal flip, shear range, zoom range, width shift range, height shift range. Now, what is going on? Well, generate batches of tensor image data with real-time data augmentation. Wow. Now, we haven't covered what data augmentation is, but we will cover that later on. Right now, we're just focusing on creating batches of tensor image data. So that's what we're focused on. We've spoken about what batches are, and when we load our images in, TensorFlow, or specifically the image data generator class, is going to automatically turn our images into tensor image data. So let's come back, as this one doesn't have a batch size parameter, because a lot of TensorFlow data loaders have a batch size parameter. I believe the next function, or the next class we're about to use, the method, we're about to use, has a batch size function. So let's create that, Shift and Enter. Now, we need to, so this is an image data generator class. It's going to automatically rescale our images using that function. Now we need a way to load them in from our directories. So let's load in our image data from directories and turn them into batches. So we can go train data equals train data gen dot. There's a method here called flow from directory. And we're using flow from directory because our images are in directories. So we'll go there. And now within this flow from directory method is 4 main parameters that we're going to look at. So directory is going to be train_dir, and then target size is going to be, I'm just going to type these out and we'll go through them in the next video. Target size is going to be 224,224. Again, this is adjustable. If you want to, you can look ahead to see what these parameters mean in the documentation. Class mode is going to be binary. You might be able to guess what that is. And batch size, of course, is going to be 32, as we've discussed. Now, we also need one of these for the test data. So I'm going to end this video here before it gets too long. But if you want to go ahead, read up on the image data generator class and read up on the flow from directory method. See what these parameters here do. And if you want, create your own test data loader using a very similar setup to this, but you may have to change the directory it's going to look at. I'll see you in the next video. Good news. Looks like my MacBook has stopped screaming at me. Classic Google Chrome. Let's continue on creating our test data image data generator instance. So did you have it a go yourself? If we want to create it, we can go test data gen.flow from directory, and then we're going to pass directory. We actually don't need to because that's the first parameter. All right, tester there, and then the target size is going to be 224, 224. Good square image. Again, that's another parameter that you could change if you want. The default one here, as you can see by the docstring, is 256, 256. And we could also change the color mode, actually. That's pretty cool. This is red, green, blue by default. So if your images were blue, green, red, you could flip it around. You can find that out, actually. That's something you would realize is if you were reading in images here and they were really blue or really green or something like that, the color values might be mixed around. So a lot of default libraries that read in images read in red, green, blue. However, that's just something to think about. If you notice that your images and you're visualizing them are very blue, have a look at the color channels and see how they are organized by default. So let's come back down here. That was just a little bit of an aside. Class mode, we're going to set that to binary because we're working with binary data. And then the batch size by default in the flow from directory method is 32, so we don't actually have to set that, but we're going to do that anyway. So let's just, right here, target directory of images, target size of images. And what does this say? Argument, target size, tuple of integers, height, width. So let's write that down, height, width. And then what does class mode say? We have class mode, one of categorical. You could imagine what is categorical if we're working with. Binary, sparse, input. The default is categorical, but in our case, we are working with binary data. So type of data you're working with. And then the batch size is size of mini batches. When you hear batches, actually, you'll also hear them referred to as mini batches. So size of mini batches to load data into. Wonderful. We'll hit Shift and Enter. And of course, we looked at the docstring from within Google Colab for this method. But if you wanted to, you could go down here in the TensorFlow Keras preprocessing image data generator class, scroll down, and you'll be able to see the methods that are associated with it. So it's actually got quite a few. Apply transform, fit, flow from data frame. So if you did have images or file names stored in a data frame, you could load them in from that. And if those those columns in a data frame pointed to different files, we've used this one, the flow from directory, just because of how our images are stored. So depending on how your images are stored, you may want to check out the TensorFlow documentation to see how you might best load images. And here's our flow from directory method. There's a bunch of different things that we could go through, but we've used some of the main ones there. There's seed if you wanted to shuffle them or transform them in a deterministic way, you could set the seed. Otherwise, it's going to use random. Beautiful. Let's go back. And after running that, we found 1,500 images belonging to 2 classes in the training dataset, because this one went first. So that's 750 images per class, and 500 images belonging to 2 classes in the test dataset. So that's 250 images per class for the testing dataset. Again, we could create, if we wanted to, valid data equals ... and split some of maybe our test data into this validation dataset. But for now, we're just going to work with training and test sets. So now that we've turned our images into data batches, let's have a look at what they look like. So we can get a sample of a training data batch by going images, labels. So this is a beautiful thing about this method as well, is because we've stored our data, how we've stored it in the pizza steak test and train style, it's going to automatically infer the labels of all the images in the steak folder training images in the state class. So let's see what this looks like. So images labels equals train data dot next. And next is basically saying get the next batch of images labels in train data. Wonderful. And we'll check out len images and len labels. 32 and 32. Wonderful. So I say wonderful a lot. We got a word to describe how beautiful this code is and learning deep learning is. So this is because of this little parameter here. Batch size equals 32. So we have 32 images along with their associative labels. So 32 images, 32 labels in each batch. Now how many, we've seen this before, but we'll go over it again. How many batches are there? So we can go len train data. 47, and this is because we have 1500 training images divided by 32. It's going to round that up. So instead of being, if the total number of images or total number of data samples you have doesn't evenly divide, it's going to just get rounded up. So the last batch may have only 15 images or something like that, whatever equates to equal 1500. And now, how about we see if this has loaded our images in and hopefully automatically rescaled them for us, why don't we have a look at what an image tensor looks like? So we'll get the first two images. So images, we'll go 2 here. So this is first 2 images of the first batch. And then why don't we also get the shape of the first image? Oh, we need images. Oh, look at that. So here's the first image. We can see that the pixel values have been scaled to be between 0 and 1. So this is red, green, blue. Then it's going to continue on for however long. This is the next image here. We've got the separator with the dot, dot, dot. And then again, this image value is in a tensor, exactly how we want it. And the values have been scaled for us. See, this is how beautiful TensorFlow is if you can think of a need in deep learning, TensorFlow has probably implemented it somewhere. And so a big need in deep learning is to load data and to scale it and prepare it for a deep learning model. With these two functions, we can load all of our training data to be ready to be used with our convolutional neural networks, which we're going to build shortly. Then if we check out the shape, it's been reshaped to 224.3. And then if we wanted to go check another images, which one should we get? Let's get number 7. Images 7. Wonderful. That's been normalized as well, or scaled. And then we can get the shape of that one. Where'd it go? It's also been resized to 224.3. Again, this is just a nice number to have. You could reshape it to whatever shape you wanted. It's just, this is going to cover the majority of our images. So that's something you'd have to look at as to what's the best. That's another value you can tune, actually. So if you imagine if we upscaled this to 512, our images may contain more data, but that means it also may take longer to compute and find patterns in. So finally, let's view the first batch of labels, and we'll go labels, see what that looks like. Okay, so they're 1s or 0s. So we can imagine we have 0 for pizza and 1 for steak. Now, that would take a little bit of inspecting. I don't know that for sure. It might be 1 for pizza, 1 for steak. But as we go through and build our model and then evaluate our model's predictions, we'll be able to reverse these into figuring out what the labels actually mean when we evaluate our model. So, with that being said, let's have we gone through the steps that we need to so far? Have we pre-processed our data? We've become one with the data. We've visualized. Now we've pre-processed our data. We've prepared it for our model. And the main step here was scaling, normalizing. And I'm going to add one here and turning our data into batches. Beautiful. So let's go on to number 3. We'll do that in the next video, actually. Create Oh, far out. Create. Step 3, create a model. Start with a baseline. All right, I'll see you in the next video. Welcome back. So we've become one with the data, and we've pre-processed our data into batches of images and labels. So now it's time, make a little heading here, to create a CNN model. We're going to start with a baseline. And have we discussed what a baseline is? Well, if we haven't, we will here anyway. So a baseline is a relatively simple model or existing result that you set up when beginning a machine learning experiment. And then as you keep experimenting, you try to beat the baseline. So before we write some code, we'll just return back to the keynote for a moment. Won't be here long. We're focused on writing code. So if we have a look at the architecture of a convolutional neural network, we have the inputs, we pre-process them into our red, green, and blue color channels. They get represented as a tensor, of course. And then if this is our simple CNN, it might only have one convolutional layer, potentially a pooling layer. You know what? It actually doesn't even need a pooling layer. It could just be a convolutional layer, and then a fully connected output layer. And then, so that could be our baseline. See how this model performs on our data. And then we try to improve to see if a larger model will work better on our data. So in this case, it's got 3 convolutional layers and 3 pooling layers. So how about we go for something in between these two? We'll build, our baseline can be a convolutional neural network with just 3 convolutional layers. And I know we haven't fully discussed what's going on with the convolutional layers. We're going to get to that in a second. But let's write some code first. So we'll come back here. Let's make the creating of our model a little easier. We've been typing out a lot of TensorFlow code that we don't necessarily have to. So from TensorFlow.keras.optimizers, we'll import atom, and then we'll go from TensorFlow.keras.layers, import dense, flatten, conv2d. What else do we need? Well, we'll use MatMul. We'll get that while we're here. And also activation if we wanted to. Oh, again, typo. We can also get from TensorFlow.keras import sequential. This is going to save us just a fair few amount of keystrokes when we're building our model. So we'll go here, make some imports. Now let's create the model. This will be our baseline, a 3-layer convolutional neural network. Excellent. So we'll go model 4 equals sequential. We don't have to type tf.Keras this time because we've already imported sequential. And then we'll go back over here. And we don't have to type tf.Keras.layers.conv2d because we've already imported it in the cell above. So we can actually just delete all of that. And we can write conv2d. Filters, I'm going to set that to 10. Again, we haven't discussed what filters is, but if you want to, again, you can look up, or you might actually know what filters is if you did the homework, if you read the CNN Explainer website, because they talk about what filters are there. But I'm just going to breeze through these and type them in. I'm going to go through them in a moment. Padding, and the activation can be, activation, I spelled that right, relu. And then the input shape is, what's our input shape? We've created it already. What's the size of our image tensor? And look at this is beautiful. We're getting a filters, kernel size, strides, paddings, or padding's not a plural. Input shape is going to be 224. And why are we putting the input shape here? Well, because it's the first layer in our neural network. Oftentimes, you have to tell your neural network. A lot of the time, actually, it can infer the input shape, but a lot of the time, you also have to tell it what the input shape is. And where do lots of errors happen with our neural networks? And it's mixing up tensor shapes. So that's why we just tell it, hey, you're getting images of 224, 2243. Activation equals relu. And again, this is filter, kernel size, strides by default is equal to 1, so we don't actually have to set that. And padding is also valid by default, so we don't have to set that either. Now, I'm well aware we haven't discussed any of this, but I just want to get through building this model so then we can go back through and talk about it. All right, activation equals ReLU, and then we're going to flatten the outputs here. So we can just pass flatten there so that our dense layer, our fully connected output layer, gets a big vector as its input, sigmoid. Wonderful. So there's our model 4. Check that out. So I'm going to write here, this is the input layer, specify input shape, and then this is the output layer because it's the final layer. Output layer working with binary classification, so only one output neuron. Beautiful. Alrighty. So there's our model. There's our simple baseline model. Now, why is it important to make a baseline? Is we'll write a note here. Or maybe we'll put it up here. There we go. Note. So a common question you're going to ask all the time is, Daniel, how do you know what architecture to use? Well, in deep learning, there is almost an infinite amount of architectures you could create. So one of the best ways to get started is to start with something simple and see if it works on your data, and then introduce complexity as required. And then, e.g., look up which current model is performing best in the field for your problem. So that's an important point here, is that just to get familiar with your data, just to make sure things are working, it's always good to just start with something simple. Like we've built here, this is a relatively simple model. It's 3 layers. Throughout your deep learning journey, we're actually going to get familiar with this in a later module. You may be working with neural networks that have over 200 layers. So we'll get to that when we come to that. But if we're working on a problem, what are we working on? Image classification. So because there are so many different ways that you can create deep learning architectures, you start with something small, something that you can control, and then research something, say, which model or which deep learning model is performing best on image classification. So that could be through a Google search, or you could go somewhere like, what's it called? Papers with Code. It's one of my favorite websites. Browse state of the art. Here we go. Now we're not going to dive into this for the time being because I want to just get focused on writing TensorFlow code. But in your free time, you can have a look at what's the state of the art. There we go, state of the art for image classification. That could be some homework before the next video. So I'll let you check out the state of the art. And in the next video, we're going to go through what's happening in this model. I'll see you then. So we've got our baseline model ready, model 4. It's just waiting to be compiled and fit on the data. But we've put in these convolutional 2D layers. We haven't quite really explained what's happening here. So we've got a few parameters: filters, kernel size, strides, padding, activation, input shape. And activation and input shape are probably the two we have the most familiarity with. Let's discuss these other ones of what's happening here. Now we're going to approach this from 2 different angles. We're going to hit the keynote. We're going to break down the conv2D layer in a text-based way. So we have some example code. Here's just a very similar line of code to what we've written. Is tf layers conv2D. We've got this one has 10 filters. It has a kernel size of 3 by 3. Stride is 1 by 1. Padding is same, which is the same as above, or sorry, this line here is the same as the above. tf layers conv2D. 10 filters. Kernel size, this parameter you can also pass in. You don't need to pass it in as a tuple because it is a square. Same with strides, it doesn't need to be a tuple. And then the padding is also the same in this one. This could be padding. Another one is valid as well. So let's explain what's going on here. Remember, this is the text-based version. So a lot of information coming at you, and this is pretty dense, but then we'll have a look at it visually in a moment. So the hyperparameter name, the filters, what does it do? Well, this dictates how many filters should pass over an input tensor, e.g. sliding windows. If you're not sure what a sliding window is, don't worry, we'll have a look at that in a second. Sliding windows over an image. So if we set conv2d to have 10 filters, there's going to be 10 filters per layer going over our input image. The typical values here are maybe 10, 32, 64, 128. The more filters you have, the more complex your model. Just like with our dense layer, the more input neurons we had. Remember, we made a dense layer before with 4 neurons here. Then we made one with 100, and it had a lot more parameters. Similar type of setup here. So the higher the value, the more complex the model. Kernel size, also called filter size. So this kernel size here, 3 by 3, is going to determine how big a filter is. So if this is 3 by 3, then the filter, we'll see what that looks like in a moment, is going to be 3 by 3. So this determines the shape of the filters, so the sliding window over the output. And then we have typical values of 3 by 3 or 5 by 5 or 7 by 7. And in this case, lower values learn smaller, more fine-grained features, and higher values learn larger features. So you could imagine this as for our pizza problem. A lower value, a smaller filter, might learn the toppings of a pizza, whereas a larger filter size might learn the edges of a pizza, so something larger. And again, we actually don't define what these filters learn as they pass over an image, so that the neural network figures that out itself. The hyperparameter name padding, if we go up here, so this pads the target tensor with zeros, if it's the same, to preserve the input shape, so keeps the amount of information in the input, or it leaves it in the target tensor as is, so if valid. So this lowers the output shape. So if you want to hold more information in your input tensor, you'd leave it as same. But if you want to keep compressing the amount of information passing through each layer, you would set it to valid. So typical values, same or valid. We'll see what these look like visually in a moment. And then strides. Strides is the number of steps a filter takes across an image at a time. E.g., if a stride equals 1, a filter moves across an image 1 pixel at a time. So the typical values for striding is 1 default or 2. And again, you can change these to however you want, but these are just some of the typical values you'll see most used in practice. So this is a text-based way, and it's quite hard to understand what's going on. So that's why we're going to. I hope you've done your homework and looked at the CNN Explainer website. But if you haven't, that's okay. Let's have a look at it together. See, it's so good, I've already got it up here. So let's choose an image related to ours. The CNN Explainer website, Learn Convolutional Neural Networks, CNN in your browser. This is an amazing website, possibly the best interactive convolutional website on the internet. So here we go. We have image input. This is pizza. Now the input here is 64 by 64, 3. So in their case, they're using 64 by 64 images with 3 color channels. You can see the color channels here, red, green, blue. And now their first layer is a convolutional layer that takes an input 62, 62, 10. So that means there's 10 filters in this convolutional layer. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, what does that relate back to? Same with us in our conv2d layer. Ours has 10 filters. Beautiful. And let's click on one of these and see what's happening. You've got to be careful with this because this moves fast. This is the sliding window I was talking about. This is a filter or a kernel. So there we go. Slide kernel over input channel to get intermediate result. So you can move it here. Oh, look at that. So as we move across the image, can you see that little square? It's sliding across. And what's happening is it's performing. So there's a little 3 by 3. Look at this. How cool is that? So this is what's happening. This is a sliding window. This is one of our filters. So if we slide this across, it's going to go across the image. It's going to output some sort of value on the right. And then it comes down and it goes across here, and it goes across here. La, 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 keeps going right across. And you can go through this and explore it yourself. I'd highly recommend it going through. But let's see what are these values? You see those values in the middle? It's important to recognize that those values in the middle aren't actually determined by us, but the kernel size is. So if we were to set this to be 5 by 5, instead of being a 3 by 3 square, this would be 5 by 5. So if we come back, this is the kernel size. So this is 3 by 3. So right now we're looking at the kernel. And if we come over here, if we click on this, you might see up in the top, this is quite hard to see, but it comes up in the top right. If you hover over this little square here, you can see a vector with kernel weights. So this is the value that the kernel gets initialized with when it starts off in a convolutional layer. So these could be completely random numbers. And then, as we get out of this layer, as our model passes the input data through layer by layer, these numbers get adjusted. So if we come right down to this convolutional layer here, whoa, look at that. The kernel weights are different. So see up in the top right where the blue comes up. So that's what we've covered so far. We've covered filters and we've covered kernels. So when we set up, there's going to be 10 filters. That means for each one of these, it's going to pass through 10 different filters. And for each filter, there's going to be a different kernel. And the kernel, the size of the kernel, is going to depend on what we've set it here. And this 3 is the same as being 3 by 3. So now let's have a look at strides and padding. We come up here, we scroll down. Now if you want a text-based explanation of what's going on in a convolutional layer, I highly recommend reading that. You can see an example there. It really does take a fair bit of playing around to understand what's going on in a convolutional layer. But now let's understand the hyperparameters. So if we have an input size, this is going to be the input size of our image. In this case is a 7 by 7 image. You can see this red square moving around? That's our kernel. You see the kernel size here? I'm going to dial that up to 3. So we've got a 3 by 3 kernel. Now if I want to, here's what we're looking at, padding and stride. If we come back to our code, we have strides equals 1, which is the same as, we could just set it like this, but I just like to see one number there. And our padding is set as valid. So let's inspect what the different values of strides and padding do. We'll come back to the CNN Explainer website. So this is our input shape. Right now padding is 0. So we say padding here. Padding is often necessary when the kernel extends beyond the activation map. This is another word for activation map, is this whatever's going on here. Padding conserves data at the borders of the activation map. So if you imagine, let's increase this to padding equals 1. We can go 2. Did you see what happened there? After padding, the shape increases to 9 by 9. So you see now how we have a border around here that's grey. This border adds a blank pixel around the outside. So that means if we had information in our image that was close to the edge, we might want to use some padding. So that way, it preserves the output shape. So see here, input 7 by 7, the light grey squares on the inside of this big square here. The output stays the same because we've increased padding to 1. But if we decrease it, the output gets compressed. So we might lose some information around the edges. Because you see here, this square gets compressed into one square on the right, this square, the next one, the next one, the next one, the next one. So let's go down to here, stride. So in our case, sorry here, if we set padding to 0, that's the same as setting it to same. So there's no padding. So the output size, I'll write down here, if same, output shape is same as input shape. If valid, output shape gets compressed. There we go. Set it to valid. Now we go here. Now you might be asking which one should I set it to, valid or same? It's by default, it's going to be valid. Again, this is up to experimentation. See which one works best for your problem. Let's come back and we'll check out the stride parameter. So right now, stride is 1. So that means when this filter takes one step, it's going to compress the output to this one square. Same thing if we go another one step, one step, one step, one pixel at a time. But if we increase the stride to 2, did you see what happened to the output shape? And then even if we increased it right up, we can't go any higher than 5. So what's happening when the stride goes to 2? So if we come here, oh, the red square on the left moves 2 pixels at a time. So that means we're compressing the information in the input into a smaller space on the output. So we keep going, keep going, keep going. Now, again, this will depend. What you set this hyperparameter to, stride, will depend on whatever problem you're working on. If your images aren't informationally dense, you may get away with setting stride to 2. If not, you can keep stride at 1. So there we go, there, across, across, across. Wonderful. So we've now covered what's going on. Filters is a number of sliding windows. Remember, a higher number, let's write this. Filters is the number of sliding windows going across an input, and then higher equals more complex model. Kernel size is the size of the sliding window going across an input, and then strides is the size of the step the sliding window takes across an input. And so what's happening here is a convolutional 2D layer is trying to, if we go back up to the top here, is trying to go across an image, and if we click on the kernel, it's trying to go across an image and detect edges, detect features. So this one here, we got maybe that's a piece of pepperoni or something, detect different parts. So that's what it's trying to detect as it goes through different layers. And so by the end, we've got an input that is being compressed into a small feature space. So look, I can't even tell what's going on here. And that's another very key point. This is a max pooling layer. We haven't quite touched on that yet, but that might be something you want to skip ahead to. So the important point here is that although this is a very visual representation of what's going on, most of this isn't defined by us. The only thing that's defined by us is the number of filters going through. And remember, if we wanted to increase these filters, we could have a more complex model. And the size of the kernel that's sliding across, whether there should be padding or not, and how big the stride is of the kernel sliding across. The rest is all figured out by the model. In other words, what features it should learn, what numbers it should set the kernel to, the different values and all of the filters and so on. So we've covered a fair bit of ground in this, but it's going to be a little bit more homework, and that is to go through this website, to play around with it for another 10 to 20 minutes. Make sure you read through it. And most importantly, write some code. Try to change these different values and step through your convolutional 2D and what's going on here. We can even check. We have to compile it first. We'll do that in the next video. But that's the homework, is to practice, is understand what's going on in a conv 2D layer by going through the CNN explainer website for 10 to 20 minutes. So that's your homework. You'll be able to find the links where you find links. But in the next video, we're going to compile this model. You might want to try and go ahead, compile this model to work with our binary classification data, and then we're going to fit it to the training data. But well done if you made it through this video. We covered a whole bunch of concepts, and of course, there's always a little bit more to what's going under the hood. But for now, we've got enough to continue building convolutional neural networks. So we've built a model, and we've gone through what's happening in each of the layers. Essentially, when the input image goes in, these conv 2D layers are trying to learn the most important features of our images. And again, we do not define the features. These are learned, or the features are learned by these layers. What's the next step after we've created a model? We have to compile it before we can fit it. So let's compile the model. Model 4, we just have to compile. So the loss is going to be binary cross entropy. Why is that? Because we're working with a binary classification problem. Our data is pizza and steak. Optimizer. See, this is a problem with working with food data sets, is it makes you hungry. I just said pizza and steak, and now I feel like a steak. And there we go. So Optimizer, we've set it as Atom. Remember, we can do this. We don't have to write it out tf as optimizer. You might want to if you can if you want to, but since we've imported Atom just up here, we don't have to write it fully out. So we'll compile it there. Wonderful. And now we're ready to step 4. 4 is fit the model. So, we want to change this to Markdown. Fit the model. Beautiful. I just want to give you a little demo of, get a summary of our model, of how the input shape changes throughout. So if we see here, what's happening is we have an input shape of 222, 222. This is because we've set padding to be valid. Right? If we wanted it to be the same, we'd set it to the same. So it starts off as 224, 224. For these two values, and then as it goes through each convolutional layer, it loses the edges. That's again because the padding here is valid. So that's just like on the CNN Explainer website. As it goes through layers, the input and output shape slowly gets smaller as it goes through the convolutional layers. So if you imagine the image starts as a square, that square is slowly progressively getting smaller towards the output layer. And the reason, we'll see it later on, we haven't got any max pooling layers here. So this convolutional neural network has a lot more parameters than the first one we built. But we're getting a little bit sidetracked here. If you want to dive more into that, I'll let you go ahead, but we're going to focus on fitting our model. So to begin, let's check the lengths of training and test data generators. We created these before. This is len training data. These should both be in batches. So we've got 47 batches of training data, and we have 16 batches of test data. Remember, our batch size is 32. So now we're going to fit the model. It's going to be, we saw these when we went through the end-to-end example earlier, but there's two parameters here that we haven't quite looked at. Train data, and then epochs is going to be 5. Remember, train data, this is a combination of labels and sample data. So we don't need to pass X and Y. TensorFlow, the fit method, is smart enough to figure out when we pass our trained data block, it is a combination of X and Y. We'll run it for 5 epochs, just so experiments are nice and fast. And then this is steps per epoch equals len train data. So this is telling TensorFlow to step through the train data, or each epoch, take 47 steps, because we want it to go through all of the batches. And then the same with the validation data. Oh, that's not how you spell validation. Validation data is going to be test data. A little confusing there. We just want it to validate at the same time as its training. Validation steps equals length test data. Oh, this is getting exciting. We're getting so close to fitting our baseline convolutional neural network. And of course, if we wanted to, we'll go to the doc string there, but you can also look this up in the TensorFlow documentation. There's a fair few things going on here. What does it say? Where's steps per epoch? There we go. The default is none. Same with validation steps. So if we come down, what steps per epoch tell us? Validation data, shuffle, class weight, sample weight. A lot of parameters here. You can dive into those if you feel like it. Steps per epoch. Total number of steps, batches of samples, before declaring one epoch finish and starting the next epoch. Okay, when training with input tensors such as TensorFlow data tensors, the default none is equal to the number of samples in your dataset divided by the batch size, or 1. If that cannot be determined, or 1 if that cannot be determined. If X is a tf.dataset and steps per epoch is none, we can keep going. Okay, so we'll let this run. We'll set that up. Oh, yes, our baseline is running. Now this should be pretty quick as well, because we've gone runtime, change runtime type, hardware accelerated GPU. I'm going to skip the video ahead until it's done, and then we'll inspect what's going on. Beautiful. So that took all of about 45 seconds. We see, okay, not too bad for a first try. Now, it's not performing as well as Model 1 because it's, what was Model 1's results? Can we still have that? Is Model 1 still saved? Model 1, evaluate. We should be able to evaluate it on the test data, right? Model 1, evaluate test data. Okay, so Model 1 has an accuracy of about 88%. And if we go Model 1.summary, it's because we've got a combination in here of convolutional, so 2 convolutional layers, max pooling, convolutional, max pooling. So that may hint that our baseline model here, Model 4, may improve if we add some convolutional layers and some max pooling layers. So, we exit out of that. We've trained a baseline model. Right now we know its accuracy score on the test data set. So if we wanted to further evaluate it, what are some classification metrics that we could do? Or what are some other ways that we can evaluate our model? I want you to have a think about that, because that's what we're going to look through in the next video, is evaluating our baseline model. By the results we got from the last video, it looks like our baseline model is learning something. Remember, with the binary classification problem, depending on how many samples of each class you have, guessing is usually around 50%. But ours is getting well over that. But of course, we'd always like to improve it. But before we do, let's evaluate it. So did you ever think about what are some ways we can evaluating our model? And all right, it looks like our model is learning something. Let's evaluate it. So did you ever think about some different ways that we can evaluate our model? I mean, one way is to check out its training curves. Another way, of course, if we go back to our keynote, is some common classification evaluation metrics. We've used the accuracy, so that's built into our compile method. We come up here. We've used accuracy here. But there are some other ones. We could use precision, recall, the F1 score, confusion matrix. Usually if we wanted to use any of these, we'd have to make some predictions and then compare them to the ground truth labels. But let's go with the plotting the loss curves option. So because we've saved our model's fitting history to this variable, we can use the history object within that to plot our model's training curves. So we're going to need pandas as PD, because it's just really easy to create a plot if we create a data frame. We'll access the history of model 4, so history 4.history. Then we're going to write plot, and we'll set up the fig size to be my favorite hand in poker, which is 10.7. Wonderful. So we got here, I'm just going to write here. Let's plot the training curves. Oh, so what's this telling us? So this is the epochs we have here. So a model, it starts off, the loss starts really high and then starts decreasing. That's what we want, because remember, loss is a measure of how wrong our model is. The higher the loss value, the more wrong our model is. But it seems as though, which one's this? This is accuracy. So this is hard to look at 4 different curves on one plot. This accuracy, the training accuracy is going up. The validation accuracy basically sits at the same all the way across. Same with the validation loss. So let's this plot's a little confusing to me. Let's separate these into separate curves. So we should plot the validation and training curves separately. This is another real important concept. Like if you're not sure of like when you visualize something, that's the whole idea of the data exploration motto, right? Is visualize, visualize, visualize. But if the visualizations that I'm making or you see someone else creates, you think, oh, these don't really make sense. I'd like to improve them to my own style. That's something you should be a big advocate of, or a big experimenter with. Remember, machine learning practitioner's motto is experiment, experiment, experiment. So we're going to create a little helper function here. We will give this one a docstring because we're good Pythonistas. So returns separate loss curves. That's a simple way for training and validation metrics. Now, of course, we could have actually, what could we have done to have this automatically done for us? We could have created callbacks equals TensorBoard callback. We could have made a TensorBoard callback. We did that in a previous video, so that may be a little extension to this notebook. But for now, we'll push through with plotting our own loss curves. So we're going to set up the training loss first. Can be history.history.loss, and then it can be the val loss. We'll do the loss. We'll do the losses first. History.history. We want val loss. So what we're doing here, I know I'm jumping around a little bit, but I just want to tell you where I'm getting these variables from. So these variables are logged. We're just taking them from here. They're just going to all be the same as what we're taking from these. So these are like in a table sort of format, but we want to visualize them like this. So we're coming down here. Now let's get the accuracy. So the accuracy is going to be we'll index the accuracy. And then the val accuracy, history.history, val underscore accuracy. And then we can set epochs, can be range, len, how long is our history object, history, and we'll get one of the items from there. How many epochs did we run for? And then we want to plot the loss. So let's do the loss first, plot loss, plt.plot, epochs on the x-axis, loss, the training loss on the y-axis, and then the label, that can be a training loss. Wonderful. And then we'll go plt.plot, epochs, we'll plot the val loss. We'll get both loss curves on the one plot, val loss, and then plt.title. This can be just nice and simple, loss, plt.xlabel, type in x as if you'd say it. And then this can be epochs. And then we do want a legend so we can tell what curve's going on where. So that's going to be the loss. Oh no, I like that entered. And then we also have to plot the accuracy. Plot the accuracy. We can actually, I know I'm a big advocate for just writing the code out, but let's just copy this, save ourselves the mundanity of rewriting it all. We're just going to change this to accuracy, change this to accuracy as well. Accuracy, beautiful. And then we want also the title can be accuracy. Now, it's also probably a good idea if you find yourself writing a lot of these different like helper functions, you can save these to like a script called helper_functions.py or something, upload it to GitHub, and then just import it every time you want to run some sort of notebook experiment. That way you're not rewriting the same helper functions over and over again. We'll probably look at doing something like that later on, because I think this one might come up at some point again. But in the meantime, let's check out the loss and accuracy of model 4. So plot loss curves, history 4. Is this going to work? Oh, why didn't that work? I want it to be on separate plots. Oh, you know what we need to do here is plot figure. We need to create a new figure. Every time you want a new figure, write plot.figure. So we just kind of recreated the same plot we have here with a whole bunch of code, and all because we didn't include this one. So let's run this. Oh, we need to rerun our function. Classic Colab notebook or Jupyter notebook. There we go. So the loss. Okay. This is much easier for me to understand because there's only 2 curves on each plot. So there's a real key thing going on here. The validation loss is, the training loss is good. It's going down, that's what we want. But the validation loss doesn't really do much here. So this is probably an important note. I'm going to write this one down. Let me get the key note. Because this way we'll have a reference to it and it's not just me saying. How do we describe this? So when a model's, put this in bold, validation loss starts to increase. So our validation loss isn't quite increasing, but it's trending that way. It's certainly not decreasing, put it that way. But when a model's validation loss starts to increase, it's likely that the model is overfitting. This is another key term, actually. Overfitting. This is overfitting the training data set. Overfitting is a problem you're going to see a lot. And we'll explore different ways to prevent overfitting. But overfitting, this means it's learning the patterns in the training data set too well, right? And thus the model's ability to generalize to unseen data will be diminished. Did I write that right? Diminished. Okay, so what's happening here? The training loss going down. Good. Model's learning on the training data set. Validation loss not going down. It's probably starting to go up. So it's likely that our model is overfitting the training data set. So that means it's learning the patterns too well in the training data set. Wow, this sentence actually makes sense. And thus, the model's ability to generalize to unseen data. So the validation data, remember, the model hasn't seen that. It's trying to learn the patterns in the training data so that it can recognize the test data. So this is what you want to have a look out for, is when your model's starting to train and the validation loss starts to go up, there's something going on. Your model is overfitting. So we're going to have a look throughout the next few lectures, or next few videos, and probably throughout the whole course actually, is ways to prevent overfitting. That's a big part of deep learning and machine learning in general. And if you want a little analogy, it's like if you were, remember do I still have this in the keynote? Yes. Remember our 3 dataset slide? So possibly the most important concept in machine learning. Overfitting is like learning the course materials far too well when you're studying at university. So if you just learn the course materials off by heart, but then the final exam comes along, in other words, the test set, and you can't do anything on the test set or the final exam, because all you've done is memorize the training set. And the final exam, your professor's like, I'm going to put this tough question on there, and it's going to be really hard for the students to get it. But if they've learned the principles, the patterns in the course material, they should be able to figure it out. That's what we want our machine learning and deep learning models to do. We want them to generalize to unseen data. And when they've learned the training set far too well, it's referred to as overfitting. If they've learned the training set poorly, so they haven't even gone well, the loss isn't decreasing on the training set, that's often referred to as underfitting. So, without further ado, let's, or actually, if you wanted to, you could keep evaluating our model. This is step 5. We've only looked at the training curves. If you wanted to figure out its accuracy and precision and recall, I'll let you do that. But what we're going to do is, in the next video, or next few videos actually, is adjust some of the parameters of our model and see if we can combat this overfitting. I'll see you then. Welcome back. Now you might notice I put a little note here. One of our keys is that ideally these 2 loss curves here, or the accuracy curves, training and validation, will be very similar to each other. That means that if the training loss was decreasing like so, ideally, so would the validation loss. It'd be a very similar curve here. It's when you have these large discrepancies between the loss curves that your model may be overfitting or underfitting. And in our case, if the training loss is decreasing, but validation loss is increasing, it tends to show that our model is overfitting. In other words, learning the training data set too well, and then not generalizing to unseen data. But this isn't actually a bad thing. In fact, let's create a new heading. That's what we're going to start working with now, is 6, adjust the model parameters. So fitting a machine learning model comes in 3 steps. And now, of course, there are many different steps, but we're breaking it down. We're simplifying it here. So step 0, we'll start from index, is create a baseline. So something simple, a simple model to just see if it works on your data. Number 1 is beat the baseline by overfitting a larger model. And then 2, after that, reduce overfitting. And so you might be wondering, okay, what are some ways we can induce overfitting? So let's write that down. So ways to induce overfitting. Now, we've seen some of these before. One of them could be increase the number of conv layers. So, in other words, make our neural network deeper. The other one could be increase the number of conv filters. So, if we come back up to where we created our conv layers, filters is the first parameter. So, filters here, we could increase this from 10 to say 32 or something like that, or even 64. This number is really arbitrary. You could make it as small or as large as you like. Will really just depend on your problem. We come down here, back to where we were. And then another way would be add another dense layer to the output of our flattened layer. And there's a few more, of course. However, really, these are probably the main knobs you're going to turn when increasing or inducing overfitting, is increasing the number of layers in your network or increasing the number of hidden units or filters in terms of a convolutional 2D layer within those layers. And then if we wanted to reduce overfitting, one way we could be, we're going to have a look at these throughout the next few videos, by the way. Reduce overfitting could be add data augmentation. We haven't looked at this yet. Add regularization layers such as MatMul 2D, and add more data, so on and so on. So we'll dive a bit more into these as we go on, but for now we're going to set up. Let's take on this one actually. If our model is already overfitting, I think it's a good time now to take down the MatMul 2D layer. So what we'll do is we'll build it first. We'll build the model first, and then we'll discuss what's going on. So create the model. This is going to be our new baseline. So we want model 5 equals sequential, because we don't have to type out tf.Variable. We've already imported some stuff. And then we're going to go conv 2D, pass it 10, 3, number of filters is 10, the kernel size is 3, because we're just not using these parameters there. We're just saving ourselves some keystrokes. Activation, of course, is going to be relo, and because this is the first layer in our model, we need to define the input shape, don't we? 224, 224, 3. And then we can go here. Now we're going to introduce a new layer, and that's the MatMul 2D. We're going to write the whole network size before. We could actually just leave this pool size as 22, but I'm going to just type in this parameter here. We'll type out the whole network first before we dive into what MatMul 2D is doing. If you want to jump ahead, you can pause the video now and check the documentation for max pooling, but let's add another convolutional layer. And this might start to look familiar to the colored block addition that we described in the keynote earlier. So MatMul 2, we don't actually have to type 2, we can just leave it like that. And then we're going to add another convolutional layer, 10, 3, activation equals value. And then we are going to add a final max pool. So you're starting to see the pattern we're doing here, is we're going conv layer, pooling layer, conv layer, pooling layer, conv layer, pooling layer. And that's a very standard approach that you'll see in many convolutional neural networks, is to have a convolutional layer, some sort of pooling layer, or some kind of activation layer, and so on and so on. It's like a remix of all the different layer types. Beautiful. So if we look at this, where have we seen something like this before? If we go to our favorite CNN website, CNN Explainer, they've got conv, relu, max pool. So they've got an extra convolutional layer in between max pooling layers, but we're starting to really replicate what's going on here. And then we hit Shift and Enter on this. Oh, I've got a typo. Activation equals relu. Beautiful. So let's have a look at the doc string of what happens in MatMul 2D. Max pooling operation for 2D spatial data. Downsamples the input representation by taking the maximum value over the window defined by pool size for each dimension, along the features axis. Okay, so that's a little bit of a text explanation, but what do we do when we want to understand something more? We can go to Visualize, click on the max pool layer here, and if we pick a random spot, so maybe here, do you see what's happening with the square in the middle? So this kernel that we're using is, you can see under where my mouse is, it's 2 by 2. So it's a 4, it's a square of 4. Then in the middle there, you have max brackets, and then a square that's 4, and you have 0.08 in the top left, 0.12, 0.1, 0.04. Then if we get the max of that, what has it done? It's reduced the number of squares from 4 to 1. So it's taken the maximum value. You see how 0.12 is the maximum value? Now, this is what happens what is that going to do? If you start to reduce, if all I'm doing is if I have a bunch of max pooling layers and I take 4 squares and turn them into 1, what's it going to do? Have a look at the difference between the input shape on the left, 60 by 60, and the output shape on the right. What's it done? If I'm changing 4 squares to 1 for every 4 squares, it's halved the output. So what we're doing here is we're condensing the input to a smaller output. And the idea of max pooling, if a convolutional layer finds features in an image, well, max pooling finds the most important parts of those features, if that makes sense. So if you look at the square I'm hovering over now, we have max, and then the top left is 0, then we have 0.09 on the right, 0 on the bottom left, 0.36 on the bottom right. The max pooling layer has taken the max value, so it's determined that to be the most important feature out of those 4 squares. So now, let's go back to our neural network code. What do we do after we've created a model? Let's compile the model, and then we want to go model5.compile. We just have to do it exactly the same as before. Should be had some really good practice at compiling models by now. Binary cross entropy, because we're working with what data set are we working with? Pizza steak. Loss equals binary cross entropy. Optimizer is our faithful atom. And then metrics, of course, is going to be accuracy. And now let's fit the model. We'll save history5 equals model5.fit. The reason why I'm going to fit it straight away is just to see how it goes. Right, we'll see the effect of what these max pooling layers have done. Steps per epoch equals len train data. And then validation data, and then validation steps is going to be len valid data. Beautiful. We'll fit this. It shouldn't take too long. So I'm going to pause the video here and then skip ahead. I'll see you once this architecture is finished fitting. All right, that didn't take too long on my end. So we've got a validation accuracy of nearly 86%. So how does that compare to our Model 4? Just off a quick site value, we go back up here. Model 4, oh wow. Just by adding those max pooling layers, we've increased our accuracy by about 5% on the validation data set. And let's not leave it there. Let's get a summary of our latest model. So get a summary. I want to really exemplify what's happening with these max pooling layers of our model with max pooling. We might go model5.summary. The most important point here is to pay attention to the shapes. So we have our input here. We've got a convolutional 2D layer. It's reduced the size by a pixel around the border. So 224 has gone to 222, 222. And then we had this max pooling layer, and what's it done? It's halved it. It's halved the size. And then again, we've got another convolutional layer, reduces it by 2 pixels. And we have a max pooling layer, halves it. So 109 is halved to 54. Convolutional layer, again, halved. Now look what's happened. What have we done here? The total number of parameters is 8,861. What did we have for Model 4? Model 4.summary. 477,000. Now, despite having, what's that? That's like 50 times more parameters, thereabouts, in Model 4 versus Model 5. Model 5 outperforms Model 4. This is the power of a max pooling layer. Now, let's see what it's done to the training curves. We can plot loss curves using our helpful function. Plot loss curves is history 5. Oh, look at that. What did we say before? Ideally, the training and the validation loss curves are very similar to each other. Now that's not perfect, you're right. but it is certainly much better than what was happening up here. Look at that. This one's basically horizontal and this one's going downhill, whereas over here, at least they're both heading in the same direction. And it looks like if we kept training for a little bit longer, they might have kept going down. Same with the accuracy. Validation accuracy looks like it's teetering off here. So what max pooling has done, it's essentially, we come back to the CNN explainer, their input, 60 by 60, it's halved it to the output. So it has really just removed the features in here. If we go over there, the edge, it's removed the features. It's only taken the max. So it's just really condensed the features so that the model has the best chance to only learn the most important features. So even though it's got a lower number of total learnable parameters, those parameters are of a higher value, or at least that's what it looks like from evaluating our model. So now that we've taken care and we've seen one way to reduce overfitting, and that's to not only just reduce the number of features in a model, but to, if we're reducing overfitting, I didn't explain this before. Reducing overfitting is also known as regularization. So that's, I'll put that in a little tidbit here. Note, whenever you hear the term, so there's a lot of jargon in deep learning, so that's what I'm trying to sort of to educate you as it's going along, is to sort of, as the word comes up, we'll use it in the context of when it's been learned rather than just bombard with definitions. Reducing overfitting is also known as regularization. So this is exciting, right? We've got tools in our arsenal. We've got tools in our arsenal to fit a machine learning model. We created a baseline. We beat our baseline by overfitting a larger model. Now we've got tools to reduce overfitting. So that's deep learning in a nutshell. Now, we've also talked about another method here, and that's data augmentation. How about we start to tackle that in the next video? In the last video, we saw how the max pooling layer condensed the features of what our model's learning by taking the most important values. So if our convolutional layer has identified some features, max pooling is going to condense them into a smaller space. So having a smaller number of total parameters to learn, but those parameters are what the model has deemed most important in those images. So now we're going to keep digging into our bag of tricks. We'll go back up to what we wrote down, was reduce overfitting by adding data augmentation. And just a little reminder, reducing overfitting is also known as regularization. And what we're trying to do here is align these loss curves, because that's the most ideal position. Because if these curves are aligned, it means that our model is performing just as well on the training set as it is on the validation set. And remember, in our case, the validation set is data the model has never seen before, which is our ideal case, a model that is able to generalize to unseen data. Let's make a little heading here. Opening our bag of tricks and finding data augmentation. All right, so what we're going to do, as always, is code something up first, and then we'll discuss what's actually happening. So to introduce data augmentation, I know we haven't even discussed what data augmentation is. You can probably have a little bit of a guess what's happening, but if you're not sure, that's all right. We're going to go through it. So we're going to reinstantiate our image data generator classes or instances. Create image training instance with data augmentation. So if you remember, when we created our train data gens, this one's going to be augmented now. And you'll be able to notice the difference of what's happening. Generator, if we read the doc string, what does it say? Generates batches of tensor image data with real-time data augmentation. Yes, that's what we're after here. So if we pass in, the first thing we want to do is rescale. Rescaling is actually a form of data augmentation. Rotation range equals 0.02. Remember, if you want to understand what rotation range is happening, you can read the doc string here. We should have rotation range somewhere in there. Anyway, it's there somewhere. Rotation range is going to be 0.2. You might be able to guess what that does. Shear range equals 0.2. I'm going to try and remove this doc string so it's not in the way of the code. Looks like it wants to appear. That's all right. Zoom range equals 0.2. Data augmentation, I'm actually very, very excited to show you this because this is one of the coolest things. I know when I first learned about it, it blew my mind. Height, shift range, that's what we want. We've done width, we've done height. What else could we do? We could do a horizontal flip. Ooh, that might reveal something of what happens, equals true. So, I'm not going to explain those for now. You can read the doc string if you wanted to have a look, or you can look at the image data generator class on TensorFlow. But this one is an instance of trained data being augmented. So now we're going to just reinstantiate our original trained data. So create image data generator without data augmentation. So we go train data gen equals image data generator. Now, we don't have to rescale, but rescaling is probably one of the most important ones to do. As we saw in a previous video, it dramatically speeds up the speed at which our neural network is able to find patterns in data. This is going to be for the test data set. So test data gen equals image data generator, rescale equals 1 to 5. Beautiful. Okay. We shift that. All we've done is reinstantiated this. We've written these two lines of code before. The only difference is this one. And so now you might be thinking, okay, Daniel, we've written this data augmented trained data gen class or instance of image data generator. Question you might have, let's get out our faithful emojis. Question equals, what is data augmentation? So let's answer that. Data augmentation is the process of altering our training data, leading it to have more diversity, and in turn, allowing our models to learn more generalizable, this is hopefully, more generalizable patterns. And altering might mean adjusting the rotation of an image, flipping it, cropping it, or something similar. Now, saying it and doing it is one thing. So let's go back to our faithful little keynote, improving a model from a data perspective this time. So this is a method to improve a model to reduce overfitting. Remember, our steps are create a baseline, overfit, reduce overfitting. To reduce overfitting, you could add more data. So that's just get more images of pizza and steak. Or we could introduce data augmentation, which is what we're covering now. So increase the diversity of your training data set without collecting more data. Increased diversity forces a model to learn more generalizable patterns. Generalization patterns. That could be generalizable. Fair few typos in here. No wonder I make so many mistakes with my code. And we're going to have a look at, actually, I was about to go to the next slide, but you know what I think will be a better option? Is we just write some code to visualize what data augmentation is doing. Because slides are boring, right? Let's come back. Right here, let's write some code to visualize data augmentation. And what we might do is, because to prevent this video from getting too long, we're going to write some code in the next video to visualize data augmentation. If you want to skip ahead, if you like, you can look up this class, image data generator, see what each of these do, and try to have a guess at what it's going to do to our images. Or even just look up a blog post on data augmentation. But if not, I will see you in the next video and we'll augment some of our images. Alrighty, we've spoken of data augmentation. It's time we had a look at what that actually looks like. I've got a slide ready to go for this, but I prefer to write code. So let's import data and augment it from training directory. And we're going to print, this is going to be our augmented training data. And we can go train data augmented, name it really simply so we can identify the difference between normal data and training data that is augmented. We're going to use the flow from directory method, which, what does it do? takes the path to a directory and generates batches of augmented data. Beautiful, that's exactly what we want. We're going to pass it train_dir, because that's our training directory. What do we set up the target size to be? It actually, you could set it up to what you want, but we're using 224, 224. And then the batch size, what's that going to be? We don't actually have to put this because it's by default 32. What type of classes do we have? Class mode. We have to set this up because the default is categorical, but we are using binary. And we're going to, for this instance, we're going to use shuffle equals false. Now this is only going to be for demonstration purposes only, just so we can see what's going on when we augment our data. And so here, because usually it's a good idea to introduce as much randomness as possible to your data set. That's why the shuffle parameter is set to true. Now we're going to create non-augmented train data batches. So we can go train data equals train data gen. This one's the unaugmented one. .flow from directory to say, hey, TensorFlow, go into our training directory, get all of the images in there, check out what the directory names are, such as train/steak or train/pizza. They're the class names. Turn them into batches of 32. And the class mode is binary. So there's only 2 classes. If you find more, error. And then shuffle. This one is also going to be false, just to demonstrate. And then finally, I might actually just print this out just so we know. So I'll put a colon there and non-augmented training data. And then finally, we will create non-augmented, this is probably a note as well, I'm going to put down, test data batches. I'll put this down in a second. Print non-augmented test data. So test data equals test data gen dot flow from directory test dir, and then what's the target size? It has to be same as the training size. We could have really put this up in a variable, so like img size equals, this is a convention you'll see just while I'm thinking of it. You might see img size as like capitals, and then you could go 224, 224, set that up as like a global variable in Python, and then we could just type in here img size, because that's the same thing. And then we might go, or we will go batch size equals 32. Again, don't need that because that's the default. I just want you to get used to understanding what a batch is. And then this one's going to shuffle automatically. It doesn't matter if the test data set. We're going to visualize the training data set. And this was the note I was going to add. I just realized this as we're coding up. What have we got wrong? Target size, that's what we need. Beautiful. So here we have it. Augmented training data, we have 1,500 images belonging to 2 classes. Non-augmented training data, 1,500 images. That makes sense because they're both coming from the same directory. And then non-augmented test data. Now that's a key point there. That's what we're going to put in here. We're going to put a little key. And note, data augmentation is usually only performed on the training data. So using image data generator, built-in data augmentation parameters, our images, this is another key point, are left as they are in the directories, but are modified as they're loaded into the model. So I just remembered both of these actually. That could really be 2 points, but we'll talk about this. So data augmentation usually only happens on the training data. So we want to make our model, we want to make it difficult basically for our model to learn what's happening in the training data so that it can generalize to test data. So if a model performs well on augmented training data, hopefully that translates to performing well on non-augmented test data. And you're like, Daniel, we haven't even seen what augmented training data looks like, and that's what we're about to do. And then finally, using the image data generator built-in data augmentation. So when our images are augmented, as we're going to see in a second, they actually don't change in the directories where we have them. So they'll stay the same there. They change as they're loaded in to our model. So without any further ado, This is really exciting. We're going to write ourselves a little message. Finally, let's visualize some augmented data. Woo! Alrighty, so we need to write some code. Let's get some sample augmented data batches. That's a good idea. So images labels equals, oh no, we need non-augmented and augmented. So the first one we'll get is train data.next. So train data, remember, is not augmented. That's this one here, non-augmented. So next, and then we'll go augmented images and augmented labels equals train data augmented dot next. And I'm going to put a note here is that labels aren't augmented, only data, images. So this is just a way to store this variable here. We could really just put underscore and use this labels parameter because they'll be the same, because this is why we didn't shuffle them, so that we know that the next batch of each is going to be the same because they'll be loaded in, they won't be randomized. Typically when we load our data in, it'll just take these two, it'll take the training file, and if shuffle was on true, it'll load files from the training folder randomly, but because we're not shuffling it, it'll come in sequential order. So whichever pizza image comes first will be loaded in the first batch. That's why we've put shuffle to false. But just to reduce confusion, augmented labels. Okay, wonderful. So now let's show the original image and the augmented image. This is again where we didn't shuffle our images, so we know random number equals random. Have we imported random? If not, we'll do it again. I think we have when we coded up our plot random image function. We want a random int between 0 and 31 because our batch sizes are 32. So we'll get a random integer between those two numbers. Or actually, I think we can do 32 because that'll go up to -1. If not, we'll get an error eventually. We're going to plot a random image from the first batch. So imshow images random number. So there we go. So we're just getting this image from the non-augmented training data, the first batch, and we're plotting the whatever random number comes up. So I'll write down here actually, just a little print statement showing image number random number. I love randomness. Love, love, love showing random images. Plot title. What title could we give this? Let's just go keep it simple. This is the original image, and then we're going to, we don't want an axis, however you pronounce that. We want another figure because we want another plot. This time we're going to imshow augmented images, and we're going to get the index on the random number, and then we're going to do the same thing, plot title, not the same title though, augmented image. Oh, this is so exciting. We're about to see our first augmented images after talking about it for about 3 videos. Was it 3 videos? And I think that's it. Let's see what this looks like. Hopefully it works. Yes, here we go. So this is image number 23. So we're working with pizza. As I said, because we've set shuffle to equal false, it's going to load in pizza first. And this is the augmented image. So let's visualize a few and then we'll discuss what's going on. See if you can pick it up. Okay, so what's happening? This is the original. This one looks backwards. Looks like it's moved, like on the edges, up here and here. And then, so that's number 11. Number 21. Oh, is that a photo of pizza? See, this is what I'm saying. We're becoming one with the data. That's, to me, that's, where's the pizza in that? So that's labeled incorrectly. So that's very interesting. So that's number 21. If we went into our pizza directory, not sure if these will show up because Colab sometimes takes a while. There we go. If we went down to image number 21, whichever one that is, we could remove that potentially and improve our pizza dataset. Okay, this one's been manipulated a little bit. So, okay, manipulated. So now we're starting to see what's happening with our images. Okay, so this one's shifted across to the left a little bit. Do you see how we're The training data already has some diversity, but the augmentation really amplifies that to really make sure if we were building our food vision app of people taking different photos, the photos might not always be the same as what we have in the training data. They might be all over the shop as someone's taking a photo. They might move or they might have different lighting. So that's what we're trying to introduce artificially with augmented data. Okay, we're getting the same. 23's come up a lot. I think there was a movie about that. Let's go back to where we created our image data generator with data augmentation. So this is where the changes to our data or the augmentations are coming from. So how much do you want to rotate an image? So this is going to rotate it around as a square. Now, of course, we could set this to 3. We could set this to 1. You might be asking, Daniel, what values do you set for this? Again, these are other hyperparameters that you can choose. You might find that I'm using 0.2 because I've used it a fair few times. I found it works pretty okay. If you go right up to 0.9, it may rotate your images too much, so that be all basically upside down. And another thing to really remember is that if you read into the image data generator class documentation, these all happen randomly. So what one, oh, I set that to 03, not 02. What one image might be rotated 0.1, and it might be sheared 0. It might be zoomed in 0.05. It might be moved to the left 0, and it might be moved up or down 0.2. So then shear, how much do you want to shear an image? Now, if you wanted to explore these on their own, you could just comment them out, right? And then you could just make the class with only a rotation and a horizontal flip. Do you want to flip an image? And that way you could see what's going on with all of them. But I'll let you explore that in your own time. I'm just introducing you some of the main ones that you might see. Zoom in randomly on an image, and then move your image around on the x-axis, and then move your image around on the y-axis. And of course, you can go through the documentation here, and it'll tell you what all the different parameters do. Rotation range, width shift range, height shift range, etc. So we'll just re-enter that to fix up the 0.3. We'll also re-enter that, and we'll get some more data, and we'll view one more for good luck. Oh, number 10. Far out, our random number generator is not giving us very random. 17, have we seen that one? I'm not sure. We come back, this was the pretty slide I was talking about. What is data augmentation? Looking at the same image, but from different perspectives. So we might have the original photo of the delicious piece of steak and some eggs that I cooked the other day. Hopefully, our pizza steak application can pick that up as being a photo of steak. Rotate, so see, that's what might happen with rotate. Shift, we might shift it up to the left a little bit. And then if we want to zoom it in, boom. So this is a little note here. There are many more different kinds of data augmentations such as cropping, replacing, shearing. This slide only demonstrates a few. So I'll leave that as some extra curriculum to look into what other different types of data augmentation is. And don't forget, when you're asking if you're not sure like how much you should use, again, this is one of those things you just experiment with. Look at examples online of where other people have found data augmentation to work and try them out for yourself to see how they change your model. And speaking of that, how about we do that in the next video? Let's train a model with augmented data. If you want to skip ahead, I always encourage you to try and skip ahead and try it for yourself before we go through it together. Try to train a model, build model 6, same as model 5. So some convolutional layers and max pooling layers. And this time when you fit it, don't use the normal training data, use the augmented training data. And if you really wanted to, plot some loss curves when you're done. But if you don't want to jump ahead, I'll see you in the next video. We'll do it together. Now that we've seen what augmented training data looks like, so we see our original image is here, we pass it through some data augmentation and it changes it up. Let's view one more just for the hell of it. It's going to be 23. Oh, number 0. Okay, so it goes over here. Now again, this might not be an ideal setup of data augmentation, like this shift from to the right, so that's the width and the height. that might not be ideal. So again, that's part of the experimentation of different parameters in the data augmentation. So we could can these two and see how that affects our model. But for now, we're going to leave it and come back down. Let's build a model that trains on augmented training data. So create the model, or actually let's leave ourselves a little note just so we know what we're doing. Now we've seen what augmented training data looks like. Let's build a model and see how it learns on augmented data. Wonderful. So create a model, and this is going to be the same as model 5, which followed the typical convolutional neural network structure. Again, I say typical. Is that the right word? Well, it's a very common structure of a convolutional neural network is to go convolutional layer like we're building now. That's the thing about deep learning, right? Is that there are some rules and tricks, but because the field is changing so fast, it's like common practices that are working today, and that's actually a really important point. The things that I'm teaching you today, you might find in a year's time invalid. There's a better way to do things, and that's a very important mentality to have. Is to not be stuck in your ways. Is to be a serial experimenter. Try new things, see how it goes. If you find something that works, good. But if you find something that's potentially better, try it, see how it goes. Max pool 2D. But yeah, back to the typical structure is convolutional layer, max pool layer, convolutional layer, max pool layer. Com 2D. And we're going to go 10, 3. Activation. Again, we're just making the same as model 5. Conv pool. That's a little song there. Max pool, yes, and then flatten, and then dense we want 1. Activation is going to be sigmoid. Why? Because we are working with a binary classification. What activation would we use if we were working with multiclass? That's a little test for you. And then we're going to compile the model. Model 6. The answer to the pop quiz is softmax, by the way. Model 6.compile is going to be loss equals binary cross entropy. How come? Because we're working with a binary problem. Pizza or steak. Atom metrics. Here's another pop quiz. If we're working with a multi-class classification problem, what might be our loss? Could be sparse categorical cross entropy, or it could be categorical cross entropy. Fit the model. History, we're up to 6. Beautiful. So 6 models so far. We are model building fiends. Actually, did we build a model 0? So model 6.fit train data. Oh, what did we miss out on here? This should have been augmented. So that's a key thing to also keep in mind, is that when you're fitting on different types of data, make sure you're when you're running experiments, that is, on different types of data, make sure your variable names are correct. I've been caught out. I almost got caught out just then. Many a times of running different experiments, wondering why there's almost no difference, and then it's because I've messed up the variable names. Equals len train data augmented and validation data equals test data. A little confusing with nomenclature there, but I'm sure you understand what's going on. Built a few models like this already. Okay, so we're ready. We've created a model, same as model 5. We've compiled it, and once we run the cell, it'll be compiled, and we're going to fit the model. I'll write a little note here. Fitting model 6 on augmented training data. So we're going to run this. Oh, what do we get? Steps per epoch, not epochs. Did you pick that up? Here we go. Okay, what do you notice first? You might have noticed that the ETA is a little bit longer than what we ran before. I'm just going to scroll back up while this is running. Back to model 4, what did we take per epoch? 9 seconds. And if we come back down to model 5 that's running live, or model 6, sorry. Oh, actually, that was model 5 that took 9 seconds. This one's taking 22 seconds. Why do you think that is? I'll let you have a think about that while I wait for this to finish, and I'll come back here. It'll only be about a second or so for you, but I'll come back here once my model is finished training. All right, so my model is just finished, and It took about 20 seconds, 22 seconds per epoch, which is almost double the amount of time the previous model took. And if we check the accuracy didn't even start off too well. I believe on model 5, what did we start off as? We started at 58 and jumped straight to 75. That was without augmented training data, and we come back down to this one. And we're 43, 54, we barely crossed 60 by the end, and validation accuracy isn't as good either. Now, I asked you to have a think about why you think it might take a little bit longer per epoch. And if you're not sure, that's completely fine. That's what we're here for, is to learn this together. It's because when our model is fit on trained data augmented, the important thing to note is that it doesn't alter the training data that we have in here. So our training data stays the same. The reason why this takes longer is because our trained data augmented class or instance augments data on the fly, so as it's loaded in. So that takes up a bit of pre-processing power of our computer chip or GPU. I believe it might actually be pre-processed on the CPU. So that's why it takes longer per epoch. So that's just something to note if you're using data augmentation. It may take longer per epoch because it has to be transformed as the model is learning patterns in it. And the other thing is, the results aren't that good. But let's check out, what are we trying to do? What were we trying to do to begin with? We were trying to reduce overfitting. We may have made it too hard for our model to learn on the training data. So what's another knob that we can turn if we discussed this before? Maybe we've put in too many data augmentation options. So again, that's just something to keep in mind. If the results aren't where you want them, you can sort of turn your knobs to go back and forth, increase augmentation or decrease augmentation. So let's check our model's training curves, because that's what we're trying to do, right? We're trying to reduce overfitting by aligning the training curves. History 6. What happens? All right, okay. They're getting a little bit closer, a little bit, they're not perfect. So the ideal one here is right from the top left to the bottom right, and for accuracy is from the bottom left to the top right. Now the perfect loss curve is kind of like Santa. Sounds like fun until you realize it's not really real. Most of the time you're going to get them like this. If the trend is going down, that's good. If the trend is going up for something like accuracy, that's also good. Now you might be wondering why our model got such poor results in the beginning. Well, first of all, we've made our training data harder to learn on, but it's also the fact that if you remember, we didn't shuffle it. So how about we see what happens when we actually turn shuffle on? Remember how I said shuffling, it's basically always a good thing to shuffle your training data to increase the amount of randomness. So let's recreate train data augmented, but this time it's going to be shuffle equals true. And we'll build another model and see how it performs. So if you want to go ahead and give that a go, train a model, just the exact same one that we've built before, but on training data, augmented and shuffled. I'll see you in the next video. Welcome back. In the last video, we trained our first model on augmented training data. However, we noted that this data is not shuffled. And it seemed that our model performed fairly poorly on the training data set all throughout. The validation data is way eclipsing the performance on the training data set, which is showing there might be something up with our training data. So now we're going to shuffle it and see what happens. So let's, right here, let's shuffle. And I want you to have a think about it before we even code it up. Just while we're talking about it now, let's shuffle our training data and our augmented training data. I better put that there, right? Because we're dealing with a few different types of data here. So just to be precise in our wordage, let's shuffle our augmented training data and train another model the same as before on it and see what happens. I want you to think about this. Is if our model's going through our data in a sequential fashion, if we look at here, if it's loading it in the order it comes in, why might it perform poorly at the beginning and then slowly start to correct itself over time? Have a think about that, and we'll see why that might be as we go through this. So let's, we need to re-import data and augment it and shuffle it. from training directory. So we can just take our train, or we'll set up a train data augmented shuffled variable, and we'll set that to train data gen, and it's going to be augmented dot flow from directory. So we're just taking the instance that we created before, which is up here, this one, train data augmented. So this is the image data generator class that has our data augmentation built in. And see how we used it here to flow from directory with shuffle equal to false for just train data augmented. We could actually append this to be not shuffled, but we won't. We'll just leave that there. So we're just setting up this exact same setup, but changing shuffle to equal true. Let's do that. Come back. This is going to be train dir. What's the target size? We've said throughout 224, 224, but again, you can change that to whatever problem you're working on. The class mode is going to be binary. We could not set the batch size because it's going to be 32 anyway. And we don't even have to set shuffle, but we're going to anyway, because see, is shuffle in here? Flow from directory. Shuffle. I can't find shuffle. That's all right. We'll just set it to string. Shuffle data this time. Wonderful. That is the default. Found 1500 images belonging to two classes. Now we have train data augmented and it's shuffled. So what we're going to do is create the model, same as model 5 and model 6. Do you see the type of experimentations we're running here? Is that we've kept the model the same for the past two experiments. What we're tweaking is the data. So that way we know if there's something different between model 5 and model 6, it's within the thing that we're changing because the models are the same. Com2D, and what are we changing? We're changing the data. One had non-augmented data, one had augmented data, not shuffled, and this one has augmented data, is shuffled. So we'll come over here, conv2d, conv pool, max pool. We actually don't need to put a 2 there because 2's by default, conv2d. We can go 10, 3, activation equals ROU. Wonderful. Max pool 2D. Oh, we are becoming experts. Look at this. You're already writing your, what's this by now, 5th or 6th convolutional neural network? You should be proud of yourself. Max pool 2D. Wonderful. And flatten. We're saving ourselves a lot of keystrokes here too by importing different modules as we need them. Sigmoid, because we're working with binary classification, and we're just going to compile it, compile the model. We could actually, if we're using the same model architecture, this is just a note to go forward, we could actually functionize this in some way because we're using the same model and we're compiling it in the same way. So we could have actually wrote a small helper function called build model or something like that. And that way we could just call that function to build our model with all these different parameters. And then we just tweak the data when we fit it. But that's a note for future us. And then we're going to fit the model. So we're up to history 7 now. History 7 equals model 7.fit. Train data, this is important, augmented shuffled. We want it to, we're fitting on augmented and shuffled data now. I really want to see what happens when we augment our data and shuffle. Epochs is going to be 5. Steps per epoch equals len train data augmented shuffled. Beautiful. And then validation data equals test data. And then validation steps equals len test data. Wonderful. And so I think, just want to go back up to the previous model. I think we didn't do this step for model 6. Oh no, we did. That's correct, len train data augmented. Forget what I said. Well, let's run this. This might take a little while as well because it's working on augmented data. Remember, when it's loading it in, it has to augment data on the fly, so that's why the epoch takes a little bit longer. So I'll let this fit, and I'll skip the video ahead to when it's ready, and I'll see you there. Oh, would you look at that? So my model took again about 20 seconds per epoch. We can see the accuracy starts off higher on the training data set and then increases pretty steadily and comes up to almost on par, or actually the validation accuracy is really good on this one. So that's the power of shuffling training data. And let's plot the loss curves. I want you to have a think. We haven't discussed why that might be, but just have a think about why is that happening. Plot loss curves. We'll get the function here. Plot loss curves, history 7. All right, okay. So there's some pretty good looking loss curves, training loss decreasing, validation loss decreasing. It does tick up a little bit here, so that maybe that's hinting that our model's starting to overfit towards the end. But let's compare the accuracy numbers here on the training data set to our previous model. So you see here, this starts at 43, reaches 55, doesn't really increase in the next epoch, marginally gets to 62 by the end. Whereas, when we shuffled the data, it starts at 56. So first of all, already beating our previous model that was on epoch 3. And then it finishes up just above 76. Now, why might this be? So let's have a think about it. If we go back to our training data file, pizza steak, if our model was to load in the training data sequentially, so without shuffling, it's going to have a look at all of the pizza images first, learn the patterns in the pizza data, the pizza photos. And then, so once it's about halfway through, once it's been through all of the pizza data, so maybe that's by epoch 2.5, it's going to go on the images of steak. And then it's going to try and figure out all the patterns in steak, but it's already learned the patterns in pizza, so it has to adjust to the patterns of steak after it's gone through the pizza images. Whereas if we shuffle the training data as it goes through, it's looking at random images of pizza and steak throughout every epoch. So it's learning the patterns simultaneously, and it doesn't have to do a backflip on itself halfway through training. So that's one of the importance of shuffling your training data. If you're getting some sort of weird results and low accuracy or something like that on your training data set while your model's training, make sure that it's shuffled, make sure that it's in the right order, make sure that it's been pre-processed. These are some of the things you want to keep in mind if your model's not performing well on your training data, from a data perspective, that is. And so now we've tried a fair few things. If we come back to where we were, adjusting the model parameters, we've created a baseline, we've beat the baseline by overfitting a larger model, we've reduced overfitting. We've seen ways to induce overfitting. We could increase the number of convolutional layers, increase the number of conv filters. We've tried to reduce overfitting by adding data augmentation, trying to get those curves closer together. And we've tried regularization layers such as MaxPool 2D. So what was our next step? Repeat until satisfied. So we might cover what other things we could do in the next video. So if we come back down to where we were, we'll scroll down. I think we've been through enough experiments for now. Let's tackle what you might want to do to keep pushing forward with this type of experimentation in the next video. Welcome back. We've trained a fair few models so far, and as always, I've added a little note to the previous one just to cement what we were talking about so that it's in text form and it's not just me speaking. When shuffling training data, the model gets exposed to all different kinds of data during training, thus enabling it to learn features across a wide array of images at the same time. So in our case, it's learning the patterns in pizza and steak images at the same time instead of just pizza, then just steak. So now, we're up to, we don't need that extra one. We're up to step 7 of the breaking it down. It is repeat until satisfied. However, I'm going to issue a challenge to you here. Because we've already built a fair few models, I'm going to write down a few steps. What we might do, if you wanted to, or have a think about it. I'm about to write these down, but just have a think out loud to yourself, or in your head, doesn't matter. You don't have to say it. How would you keep going? How would you improve our model's performance? We have looked at a slide. I'll show you what it looks like. Improving a model. There are some things, common ways to improve a deep model. We could add layers. increase the number of hidden units. These are talking about dense layers, but how does this relate to a convolutional neural network? Could we change the activation functions? Well, we've seen ReLU works pretty good. Could we change the learning rate? Well, at the moment, it seems like our convolutional network's learning pretty good with the default atom learning rate. So the main probably 4 out of this would be adding more layers, so potentially convolutional layers and max pooling layers. Increasing the number of hidden units, which in our case would be filters for convolutional 2D layers. If we had more data, that would probably be really good. And then if we did have more data, we'd probably try and fit for longer. So let's write some of these down. Since we've already beaten our baseline, there are a few things we could try to continue to improve our model. So one of them would be increase the number of model layers. So e.g. add more conv 2D / max pool 2D layers. And then we could also go increase the number of filters in each convolutional layer. E.g. we could go from 10 to 32 maybe, or even 64 if you were feeling adventurous. Again, these are not numbers set in stone. These are just common numbers you'll find in practice. A lot of them are found through trial and error. And then we could train for longer. Right now, we've only trained for 5 epochs. So maybe the first step would be just keeping the architecture the same and training for 10 epochs instead of just 5, so double it up. We could find an ideal learning rate using the methods we've looked at in a previous video. But it seems at the moment the default one for Atom is working pretty well. Again, when the TensorFlow developers build the library, they often use really good defaults in the classes and modules that they build. We could get more data, so give the model more opportunities to learn. You could perhaps take some photos of your own pizzas and their own steaks that you've cooked and add them to the dataset and see if that influences. We could also use transfer learning. Now we haven't seen transfer learning yet, but we're going to cover that in a future module to leverage what another image model has learned and adjust it for our own use case. So there's a bunch of options you've got here, but I think the challenge I'm going to issue for this video is this is a practice. So practice can be recreate the model on the CNN Explainer website, which is the same as, I believe it was Model 1 up above, same as Model 1, and see how it performs on the augmented shuffled training data. So that's your practice. So there's a fair few things you could try. So I can't stress enough how important it is to just try these things out yourself. But yeah, give that a go. You can go to the CNN Explainer website, or you could just scroll back up and copy Model 1. But I'd highly recommend just trying to build the model yourself. We've got a convolutional layer with ReLU, conv layer, ReLU, max pool, conv, ReLU, max pool. And then these layers, convolutional layers, use 10 filters. You might want to see what happens if you increase it to 32 filters for your conv 2D layers. So there's a little challenge to you. In the next video, we're going to have a look at how we might make a prediction with our trained model. Because on custom images, because right now we've only worked with the pizza steak data set. What if we had another image that we've just taken of our delicious steak or pizza or something like that? We want to see how our model performs on our own data. So have a go at this, and I'll see you in the next video. All right, we've covered a mammoth amount of creating CNN models and training them and whatnot, but the real end goal that we're trying to work towards is creating a neural network that we can use in our food vision app. So let's give it a go. Let's try out, we'll make a little heading here, making a prediction with our trained model on our own custom data. So this isn't part of any data set, right? This is our own custom images. Because after all, what good is a model if it's not working on your own custom data or the data that you want it to work for? So let's remind ourselves of the classes we're working with. of course, we know, but we just want to make sure the class names variable is how we want it. So we've got pizza and steak, beautiful. That's stored. We created this way back when, probably somewhere up here, getting the data and inspecting the data. Now what we're going to do is get an image. So view our example image. So I've created some of our, you've probably seen this image before, but I've got some images saved in the TensorFlow Deep Learning. So if you go to the GitHub repo, of course, the links will be where you find links. And in the images folder should be number 3. We're going to try it on steak. So if you click on this, this is how you get an image from GitHub. You go download. We're going to copy this link here. Copy that. There's a beautiful, delicious steak that I cooked the other day with some eggs. And we're going to wget and pass that link in. It has to be the raw.github user content one. So if you've got just a GitHub link and it doesn't say raw, it might not work. So we're going to go steak equals mp img dot mread, and we're going to go o3 steak, just this file name here, dot jpg. And if you don't have mping, write this, import matplotlib dot image, oh no, from matplotlib dot image, import mpimg, which stands for, I think it's matplotimage. Does that work? Oh no, cannot import name. Let me scroll up, mpimage. Oh, import as, my bad. See? Even though I don't know these things off by heart. So let's scroll down here. And we're going to paste that there. Wonderful, we'll run that. Does it work? It doesn't work, what happened? No such file or directory, o3 steak.jpg. What did we get wrong? Why did that not work? Do we have it saved here? Oh, there it is. What is going on? Oh, .jpeg. I forgot the E. Okay, that's all right. Then we're going to plot imshow. This is going to be from matplotlib. Again, if you don't have this, we need to import matplotlib. I know this one off by heart. Oh, Google Colab's helping me out. Thank you. Imshow. I'm going to do steak. plt.access. We're going to turn that off and write false. Now, before we run this, if you wanted to get your own image, you can also upload a file here. So there we go, upload to session storage. Just be aware that if you exit Colab or it runs out of, the Colab runtime runs out, all of these files are going to get deleted. So just be wary of that. If you upload anything to here, if you download anything, it's going to go eventually when Colab closes your runtime. So that's why I've stored it on GitHub here. So let's run this, let's view it. It's going to re-download it, of course, because we've got the download code there. Beautiful, there's our image. Looking the same, just a little bit smaller. And so now, what do we have to do? Can we pass this? This is a pop quiz for you. Can we pass this directly to our model right now? I'm just checking the shape of it. It's a pretty large image. So this might be a little bit of a hint. Or if we have a look at what it looks like now, steak, what do the pixel values look like? Can we pass this? It's an array. You know, neural networks and convolutional neural networks, like they can't read just images. They need to be in an array or a tensor. So I'm going to leave you with that question. But if you want the answer, you can go up and I would say, look in here, inspect the data, or an end-to-end example. And that'll tell you whether or not we can use it straight away. In the next video, we'll go through the answer. Did you figure out the answer? Can we use our steak image as it is and pass it directly to our model? Why don't we just try? Great idea. Model 7.predict steak. What happens? Oh no. What do we get? Input 0 of layer 6 sequential. Sequential 6 is incompatible with the layer. None min and dim. Found and dim equals 3. How do we fix this? Well, we're running into a shape issue. You know what? I believe it's because we've loaded in our steak image and it's only got dimensions height, width, color channels. But what does our model expect? It's expecting a batch size as well. So what if we pass it tf expand dims stake, and then we want to expand it. Or actually, let me show you what this looks like first. If we go tf.expand dims, will this work? Axis equals 0. Let's see what happens. Typo. There we go. Okay, now we've got a dimensional 4 tensor. And if we go shape, what does that give us? There we go. Okay. So what if we pass this expanded stake equals that? We want to get rid of shape. Wonderful. And then we get our model to predict on expanded stake. What happens? Input 0. We need to reshape it. Okay. We can fix this. Let's write. We need to pre-process our image. So this is an important point. I'm going to write a note down here. So I'm actually doing this one during the video rather than after it. So note, when you train a neural network, I believe we've discussed this before, and you want to make a prediction with it on your own custom data, it's important that your custom data or new data is pre-processed into the same format as the data your model was trained on. Beautiful. Okay, that's the missing piece here. So now what we're going to do, how about we create a little helper function to pre-process our data. So create a function to import an image and resize it to be able, because that's another point here, this image is massive, 4,000 by 3,000, and what's our model trained on? 224 by 224, so there we go, 224, 224. So there's a big discrepancy there. The shape of our tensors aren't aligned. And resize it to be able to be used with our model. Wonderful. So we're going to call this def load and prep image. We'll pass it a file name, which can just be like the string file name, something like that, nice and simple. And im shape can be 224. Wonderful. And then we'll leave a doc string. So reads an image from file name, just a one-liner, and turns it into a tensor and reshapes it to im shape, color, channels. Does that make sense? That's not very Pythonic. It's going across the line of some sort. Maybe that'll do. Okay. Now, to harness this, we're going to use a module we haven't quite used before. Read in the image, but it's nothing you can't take on. It's going to be tf.io. IO stands for input output. It's got a little function in here, a method in here called read file, which we can pass a file name. So it reads and outputs the entire contents of the input file name. That's what we want. And we've got here, read file, file name. So file name is a tensor of type string. So if we pass it a string, it's going to read that file. All right, that's what's going to happen. And then we can decode the read file into a tensor. So we can go image equals tf.image. So TensorFlow has a lot of modules that are dedicated towards certain types of data. So when you're going through the documentation, you're like, hold on, I want to load some tabular data. Well, TensorFlow probably has a module for that. And if you want to load some image data, well, you might want to look into TensorFlow image. And then the same thing for other kinds of data. So image decode.jpg, because our image is a JPEG. We might, does it have a decode image function? That's probably more generic. Yeah, detects whether an image is a B. Yeah, I think we'll use decode image instead of decode JPEG. We'll pass it our image, and then we'll go resize the image. Image equals TF. We've done some reshaping before, but we can use the image module. It also has a resize image, and then we're going to go image shape. So this is saying resize, passes a file. Where is it? Resizes images to size. So it's going to be size. Oh, well, that doc string's getting a bit skew with. And then we're going to go image shape. Wonderful. And then finally, what else do we have to do? What do our pixel values look like right now? Code, stake. They're between what? 0 and 255. But what do we need them between? We need them between 0 and 1 because what's our model trained on? Images with their pixel values scaled between 0 and 1. So let's do that. Rescale the image and get all values between 0 and 1. Wonderful. Image equals image divided by 255. Return image. Wow. So we went through a fair few steps there, but if we break it down, what are we doing? We're reading in an image from a file name. We're decoding it, turning it into a tensor, and we're resizing the image, tf.image.resize, and then we're passing it im shape, which is 224. We've hard-coded that up here. Of course, we could change that if we wanted to. Then we're rescaling it to be between 0 and 1 by dividing by 255. Now, you might be wondering, Daniel, how did you know where to create this function? Well, I searched. So if I went TensorFlow, how to load images. And then if you go load images, might not be this exact tutorial, but if you scroll through, TensorFlow has a lot of information on loading and pre-processing data. So depending on what data you're working on, I'd suggest just searching it up. TensorFlow how to load CSV or TensorFlow how to load text, and then going through the documentation and trying it out for yourself. You might stumble across a function very similar to this, and of course, you can adjust it to your needs. So now we've got a function to load in and pre-process custom images. Let's try it out. Load in and pre-process our custom image. So this is very exciting. I love when we create a little helper function to help us out. Load and prep image. And what was the file name? Come over here. O3 stake. We've got 2 copies of that because we downloaded it twice. No trouble. It's going to be o3 stake.jpg. This is really fun. When you start to be able to use your neural networks on custom data. Oh, look at that. That is what we want. Load and prep image, working like a boss. Shape 224, 2243, and pixel values. Have a go at that. All between 0 and 1. Okay, this is what's happening. We're using our model with it. Let's make a prediction. Let's just pass stake right in here. Model7.predict stake. Oh, what? You know what we have to do? Expected min and dim and 3. Oh, sorry, 4. And ours is 3. What we're going to have to do is, we could have built this functionality in there maybe. Expand dims, but we won't because if we don't want to expand the dimensions, we don't have to. There could be a boolean in there to put this in there. This should work. You ready? Our trained convolutional neural network on our own image, or my image, of stake. And of course, you can try this on your own images. What's it come up with? Array. What's that? Where have we seen that before? I'll give you a second to think. You know what that is? It's a prediction probability. So, in other words, this means how likely the image belongs to one class or another. And so since we're working with a binary classification, if the prediction probability is over 0.5, which it is in this case, the prediction is most likely to be the positive class, so class 1. But you're like, Daniel, our classes aren't called 0 or 1, they're called pizza or steak. Well, in our case, they're probably in alphabetical order. So my guess is that if we go into the training file, that class 0 is pizza and class 1 is steak. So how about in the next video, we write another little helper function to sort of decipher this prediction probability, and we want to see it with the image. So yeah, that's a good idea. Let's try that in the next video. So we've written a little function to help us load in images and pre-process them so they can be used for our neural network. But right now, our Model 7 convolutional neural network is outputting prediction probabilities, which is very helpful for us, but we still need a way to reinterpret these in a way we can understand. And I'll just show you where we have seen this prediction probability before. So if we come back to the keynote and we find the magical slide We'll go back here. Boom. There we go. So this is very similar to what we're working on. In fact, it's the same image. So we resize it to 224, 224. And then, so this is coming full circle. This is so exciting. I'm so happy we're finally getting to explain this, because I know when you first looked at this, you're like, whoa, what's going on? Because that's what I looked at these things and was like, holy, there's too much going on. But now we're connecting the dots. We're all bringing it back together. So we bring this in, we pre-process it, we turn it into batch size, width, height, color channels. There we go. 32. 32 is a very common batch size, as we found out. 32 is good for your health. 224, 224, 3. We normalize the pixel values, that's our inputs to our model. When we pass it to our machine learning algorithm, which is our CNN that we've used, very common, very helpful, very popular machine learning algorithm because it works on image data, then our outputs are now prediction probabilities. And in this case, this makeshift model on a Keynote got it correct. It comes out looking something like this. Now, I know this is for 3 different classes. We're working with binary, but the principle remains the same. Again, these will vary depending on the problem you're working on. So, coming full circle, let's go back. Let's now write some functionality to transform this prediction probability into something that we can understand. And you know what? We're gonna follow our Data Explorer's motto. It's visualize, visualize, visualize. Since we're working with images, let's create a function to plot our image and view the class name. First, we'll write a little note here to tell ourselves. Looks like our custom image is being put through our model. However, it currently outputs a prediction probability. Wouldn't it be nice if we could visualize the image as well as the model's prediction? You know what? That would be nice. So let's do it. Remind ourselves of our class names. And then we're going to go class names, which is pizza and steak. Beautiful. And then what we can do to really just show you to convert this, we can index on these class names to figure out which one is our model predicting, which class. So we can index the predicted class by rounding the prediction probability and indexing it on the class names. Boom. So pred class equals class names. And then we're going to go int tf.round to round a tensor on, we didn't even save this to pred actually. I'll save this to a variable so we don't have to retype out that mumbo jumbo. Pred. And then let's see what this looks like. Oh, it would be helpful if we visualize that. What do we get? Steak. Yes! Oh, how cool is that? But we're not finished yet. We are not finished yet. So that's just saying the pred class is steak. So how cool is that? Our custom image. We passed it through to our convolutional neural network. It's getting it correct. This is mind-blowing. Machine learning is already exciting, but when it starts to work on your custom data, that's when it really takes off. So now let's create a function called pred and plot. Nice and simple. It's going to take in a model, file name, and class names, which can be just equal to class names. So we don't have to set that later. And then what can we do? We can write imports an image located at file name, makes a prediction with model, and we'll go down here, say Pythonic, and plots the image with the predicted class as the title. Oh yes, these are my favorite kind of functions to write. So we're going to import the target image and pre-process it. Luckily, what did we create in the last video? IMG for image can be load and prep image, file name. And then we're going to make a prediction, and we're going pred equals model.predict. And then we have to expand the dimensions, because remember what we had to do up here? Our model expects a 4-dimensional tensor, whereas our load and prep image returns a 3-dimensional tensor. Expand dims, IMG, axis equals 0. Remember, so many of the errors you're going to run into in deep learning is tensor mismatch shapes. So get the predicted class. So we can just copy this same functionality here. So pred class equals class names. We'll index onto class names. We'll go int tf.round pred. So what that's doing here, you see this? This is just rounding that to 1. So tf round that to 1. It's saying, well, I'm predicting this class. And if it was below 0.5, you could go, well, it's going to round it down to predict pizza. And of course, that cutoff, you can actually change that. So if you wanted like only round it to, if it's over 0.8, it's class 1. But if it's under 0.8, it's class 0. But that depends on what sort of problem you're working on and what sort of cutoff you want to create. For ours, this will do. And then we're going to plot the image and predicted class. Plot.imshow image, plot.title, what's it going to be? We'll call it prediction. Prediction can be pred class, wonderful. P.axis can be false. We don't want to plot the axis. Oh, yes, our function is ready. Are you ready? We're going to test our model on a custom image. So pred and plot model 7, and then the image can be o3 stake.jpg. And class name should be hard-coded. So fingers crossed this works. Yes! I'm about to clap, so I was like, I'm so excited, but I didn't want to cause the microphone and cause a disturbance in your ears, but just, we'll give ourselves a little clap. Look at that. How cool is that? We trained a neural network on some data we found on the internet, and it now makes predictions on our own custom data. So let's not leave it at 1, right? Let's not leave it at 1 image. We're going to come back to the GitHub. Of course, the links will be where you find links. We're going to come to images, and let's pick Pizza Dad, right? Because we've got a few. So by the way, the O3 is to do with the notebook we're working on, see O3. So the O3 images are going to be related to this notebook. So if we come here, let's pick Pizza Dad. And we're going to go download. There's my dad, 2 thumbs up. Hey Dad, let's copy this. And a nice big pizza in front. It's actually a delicious pizza from a cafe. That's the downside of working on food vision, is it makes you hungry. So let's download. Actually, we'll put a little excited note here. Our model works. Let's try it on another image. This time, pizza. And of course, wouldn't be complete without an emoji. Download another test custom image and make a prediction on it. Oh, I'm getting very excited, if you can't tell. wget Pizza Dad, yes, this is it. And now, look what we've got. We've got pred and plot. This is how powerful a helper function is. Model 7. And we're going to read in O3, just this file name here. O3 Pizza Dad .jpg. You ready? It's going to download an image and make a prediction. 3, 2, 1. Image downloaded. Prediction pizza. Yes! 2 thumbs up. Woohoo. That is amazing. Congratulations. You've trained your, well, it could be your first convolutional neural network, but I guess I'm betting that it's your first convolutional neural network. If it's not, but it probably is your first one to detect images of pizza and steak. So, what kind of problem did we work through? Oh, I love that so much. We just worked through a binary classification problem. So what you might be thinking is, how do we adjust what we've worked on to multi-class? So look, we've been through a fair few steps. So how about what we might do in the next few videos, we probably won't take as long this time because we've had a bit of practice, is we're going to go through a multi-class classification problem. Let's step things up a notch. Let's make it harder for our model to identify, our food vision model to identify different pictures of food by adding more classes to the mix. So we've worked with steak and pizza. How about you think of some other foods? What are some other foods that you'd like to see? I mean, I've kind of already made them, but just think of some of your favorite foods. They might be in this problem that we're about to work through. So stay tuned for that. I'll see you in the next few videos. Give it a go at predicting on your own custom image. If you want, you can upload a file to Google Colab. Just don't forget, once Colab exits, that file is going to be deleted. So take a photo of a pizza that you've eaten, or maybe a steak that you've cooked, and see if the model can predict whether it's a steak or a pizza. I'll see you soon. You put in an amazing effort so far. I mean, look at this, 2 thumbs up and a victory pizza. But what do we say right back at the beginning? Here's what we're going to cover broadly. So we've got a data set to work with, pizza and steak, yes. We've been through the architecture of a CNN, yes. We've done an end-to-end binary image classification problem, pizza versus steak, yes. We've been through the steps with modeling with CNNs. Now we're up to an end-to-end multi-class image classification problem. So let's go back here. We'll write ourselves another heading. Multi-class image classification. And so what we're going to do is we're going to change the data set we're working with, but we're going to do all of the same steps we've done for binary classification and step it up a notch for multi-class image classification. Now, before we write any code, and this is a rare exception you'll find with me, I want you to have a think about how we might change our models, and that is, the exception is talking about a concept before writing code. How would we change our model to go from binary classification to multi-class classification? Just have a think about it, about the things we've talked about. And once you've had a think about it, push forward with the video. Let's start to write some code. Here are the steps we're going to go through just as a little reminder. So what's the first one? Become one with the data. 2, pre-process the data. So get it ready for a model. 3 is create a model. Start with a baseline. Number 4 is fit the model. So we'll make sure it works on the data. More specifically, we want to kind of overfit it. Overfit it to make sure it works. Remember, overfitting is when a model learns too well on the training data and doesn't generalize well, but then we can fix overfitting. Overfitting is generally a good thing because it means our model's learning something. Then we're going to evaluate the model. Number 6, we will adjust different hyperparameters and improve the model. Try to beat baseline / reduce overfitting. And then number 7 is, of course, repeat until satisfied. And as you know, because we're serial experimenters, right? And so these steps are just guidelines. They're not set in stone. You can jump back and forth between them wherever you want, but this is just something that we can push forward with. When you're learning deep learning, there's a lot going on, so it's good to sort of have these little frameworks that you can work to get the foundations down pat. And just a little note here, we've just been through a bunch of the following steps with a binary classification problem, pizza versus steak. Now we're going to step things up a notch. I'm doing a lot of typos here. Should have typed this out before, but we're typing it out together. Step things up a notch with 10 classes of food. Multi-class classification. Beautiful. That's about as much information as we need. All the data is going to come from Food 101 as well. So what do we have to do first? Well, refer to our little steps, become one with the data, but we should put import and become one with the data. So where is our data? Well, if we go to dbourke.link /tf course GitHub, this should take us to the TensorFlow GitHub. Beautiful. By the time you watch this will probably be a lot more prettier, but essentially this table is going to stay much the same. So we're up to course materials, we're up to section 3, TensorFlow Computer Vision. Now we've got the pizza steak data set, that was our binary classification. Now we need the link to the 10 food classes all data. So I'm going to copy that link address there. I'm going to come back into the Google Colab notebook. And now, if you want to see how this was created, this data set, it won't always be created like this for you. Remember, in the extras, there's a notebook here called Image Data Modification. That's how this data set was made. So let's go into here. We're going to import zip file, and then we're going to download or copy that link that we just copied there from the GitHub. So if we come back, we'll go to this beautiful looking table. I just did copy link address. Again, all the links you need will be where you find links. So let's go here. Now we're going to unzip our data. So we can do that by going zip ref equals zip file dot zip file 10 food classes all data.zip. Then we could actually functionize this, or we could actually just use the zip on the command line, but that's all right. We'll just do it this way. Zipref dot extract all, wonderful, and then zipref dot close. All right, there we go. So that's going to download. It should be pretty quick because it is stored on Google Storage. Here we go here. Google Storage, CTM course, food vision, 10 food classes all data.zip. And what does that look like in our files? There we go. 10 food classes, all data. Wonderful. We could inspect it through there in Colab, but that's relatively slow. Let's write some code to check it out. So import OS, and then what can we do? Let's walk through it just like we did. Walk through 10 classes of food image data, and then we'll go for dir path and dir names, file names in os.walk. Let's go, we'll type in the food, 10 food classes, all data. This is what we just downloaded. And then we want to print f, we'll do an f string, there are. We could also functionize this actually. That would be very helpful, but let's have some practice writing out some code, right? That's what we're all here for. Directories, so dir names is going to tell us how many directories there are. Directories and len file names. File names is going to tell us how many images there are in each file. In dir path is going to tell us which class those images belong to in dir path. But we actually have to have this as a singular string, otherwise our f string is going to get a little confused. There we go. So let's run that. Oh, what have we got wrong here? Oh, do we need a squiggly? Yes. No, we don't need a squiggly. We need just a curly. Wonderful. So there are 2 directories and 1 images in 10 food classes all data. I bet you that 1 image is actually just the DS store, that little pesky file that appears on all Mac files. Yes, there we go. So there's the 2 directories there. And this is that pesky file. You don't actually have to worry about that one. By the time you get this data for the course, I'll probably have removed that from all of the directories. So let's just ignore that for now. But if we can see here, there are 10 directories in total in the training data set, and there are 0 directories and 750 images in the 10 food classes all data trained steak. So 750 images of steak, 750 images of chicken wings, fried rice, ice cream, ramen, sushi, hamburger, chicken curry, grilled salmon, pizza. And then for the test data set, we have 250 images per class. Wonderful. And again, all of this comes from Food 101, the Food 101 data set, which you can find on Kaggle. But I'll let you follow through the steps there if you want to download it and pre-process it yourself. Right now, we're just going to work with some already pre-processed data into the file structure that's very common for image classification, is to have your data set in train and test, and then the different classes are the file names for whichever image is inside that particular subdirectory. Now, how would we inspect these further? Well, let's set up the train and test directories. We're going a little bit faster this time because we've already been through some very similar steps with the binary classification problem. So we're kind of reiterating what we've been over already. So if the pace seems a little bit faster, don't worry, I'm sure you can keep up. It's nothing we haven't covered before, except that we're working with a little bit different data. So set up the train and test directories. This is the new data sets that we're working with for the training file folder and the test folder. Wonderful. And now let's get the subdirectories. These are our class names. We could actually just get this from the TensorFlow image data generator object. Yeah, how about we do that? We don't actually want that. Let's just start to visualize. Remember our motto of data exploration? Visualize, visualize, visualize. We have a function above, or actually, I think this is why I see why we want the list. So ignore that for a second. Let's get the class names. Before we even import them into TensorFlow, we'll get the class names. So we want path lib I'll show you one way we can do it without TensorFlow. How about we do that? Import NumPy is NumPy. The data dir is the pathlib.path. I'm going to turn the training directory into a Python path object. And then I'm going to get the class names. I'm going to turn them into an MP array, because that'll help out our function in a second. We'll turn them into a sorted list because we want our class names in alphabetical order. And we want item.name for item in data dir. Data dir is just this path, Python path. .glob, which is like a funny word for like path tree. So if this was like test, stake, image 1, image 2, glob is like a name for that. Well, that's just how I understand glob. You might have a better definition for that. And it's also funny to say glob. Print class names. You'll see what this comes out as anyway. So beautiful, we've got a list of class names. Now, of course, we could get them from just our TensorFlow image data generator instance, which we're going to create probably in the next video. But this is how we'd get them if we didn't have TensorFlow and we just wanted to use NumPy arrays and Python path objects. So now we can use our image equals view random image. We created this function before. Should have really set up a doc string so we know what's going on. But we'll set the target directory to be trained-dir. And then the target class is where random is going to come in. Random.choice. And our class name list is going to come from. So you might be able to guess what that does. If you're familiar with random. If not, what do we do when we're not familiar with something? We write it out. Random.choice class names. What's it going to do? Fried rice. We run it again. Ice cream. What's your favorite food? Hamburger. Very close. I do like hamburgers. And then we go there. And let's run this. What does our image look like? Oh, look at that. So there's the file name. There's the image shape, 512.512.3. And it is steak. And we go again. Fried rice. And so this is how we're getting familiar with our data. We're working with a new data set. So what's our Data Explorer's motto? Visualize, visualize, visualize. And so this is where we've built our handy function here. And remember how I said I really love visualizing random data. That way you're getting a good overview of the different types of images that you're working with. We're getting a lot of steak images here. Chicken curry. Let's see, we got ice cream? Nope. Ice cream? Yes, haha, what a guess. And so, of course, you could expand the view random image function. If we're working with multi-class data, you could make it view random images, and you might want to plot a subplot here of 5 images at a time so you can look at multiple different classes. It's totally up to you. But after going through this, you should start to be a little bit more familiar with the different classes that you're working with. So, okay, sushi, there we go. Hamburger. So there's a lot of noise going on here. It isn't necessarily just an image of pure hamburgers. We've got a drink cup and some fries there. What else do we have? Hamburger. Okay, again, a lot of noise going on here, but there's clearly a hamburger there. So these are the sorts of things we want to start checking out. Fried rice, that's pretty okay. That's a pretty clear image. Grilled salmon, okay. That could be quite a difficult image because, I mean, I'm not sure what that is. I'm not sure what that is, but we've got some lemon, some grilled salmon. The plate could be some interference to what our model's trying to learn. We'll do one more for good luck. And then finish off with steak. Wonderful. Okay. So let's have a look at the steps that we've been through. Become one with the data. Of course, we could keep visualizing images for as long as you want. There is we've got 10 classes and 750 images. So there's 7,500 training images. So you could be here a while, hence why it might be a good little extension to expand this to do multiple images at a time. But let's not hold ourselves back here. We're up to pre-process the data. Now I want you to try and go ahead with this before I catch up to you in the next video. We've already been through it, right? But the thing we're going to have to change is now we're working with multi-class data. So potentially if you want to skip ahead, go back to this step, pre-process the data, prepare it for a model, and just run the exact same code, but change it to work with the current data that we're working with. So give that a shot, and I'll see you in the next video. All right, so we've been through a bunch of different images. How about we just do one more for the hell of it? Why not? Oh, chicken curry. And one more for good luck. Ramen. Delicious. I had some of the best ramen ever when I was in Japan. But let's not get distracted. This is a problem with working with food data. It makes you hungry. Let's pre-process it. So we've seen a bunch of different samples. We've made sure that our image data directories are in the right format. Let's set up our TensorFlow data loaders. So we'll come here. We need to go from TensorFlow.keras.preprocessing.image import image data generator. And then what are we going to do first? Let's remind ourselves of our workflow. The steps in modeling with TensorFlow: get data ready, turn it into tensors, turn all data into numbers. Neural networks can't handle images, yes. Make sure all of your tensors are the right shape. What shape are we using? We'll see that in a second. And scale features, normalize or standardize. Neural networks prefer normalization. In other words, get the tensor values between 0 and 1. So let's have a look. Rescale. How do we do that? Well, we go train data gen. I hope you had an attempt at this yourself by referring to the code we wrote before. But if not, let's do it together. So we need to rescale our training data. Remember, in our image's current form, the pixel values are between 0 and 255, so we have to divide them by 255 to get them, to scale them between 0 and 1, which is also sometimes referred to as normalization. Image data generator, rescale 1 divided by 255, wonderful. And now we're going to load data in from directories and turn it into batches. What's our favorite batch size? Well, 32 is good for your health, but again, your batch size will depend on the problem you're working on and also the amount of compute power you have. Train dir, but that will be something that you get familiar with when you start to work on your own projects. So this is our target size, 224, 224. Remember, this is not set in stone. We could really set this to whatever we want, but this is a relatively good size for a lot of sort of baseline image classification models. Because look at our current image shape is 384, 512 for that photo of ramen. And again, there's 3 color channels. And this photo of ramen is 512, 512. So it's gonna make this image a little smaller. It's gonna go to 224, 224. But that's okay. We'll go batch size equals 32. We're going to set the class mode. What is it? This is probably the only parameter we needed to change from the binary classification. We could actually leave it as the default. Why? Because class mode equals categorical, which stands for, do we have here, what does it say in the docstring? Class mode. One of categorical, binary, or sparse. Categorical will be 2D, one-hot encoded labels. See, again, that when you read these things, right, without extensive experience, you might read it and go, wow, I didn't understand a single word in that. See, this is why I'm a big fan of writing the code and seeing what comes out and then lining up what you see with what the description is. So let's just ignore that for the time being. Our data set is categorical because we're working with multiclass, not binary. Test data equals test data gen, wonderful. Flow from directory, test dir, and then we're going to go target size equals 224, 224, and then we are going to go batch size. We don't really have to set the batch size because the default is 32. Hey, look at that. Thank you, docstring. But we're going to anyway, just so we get familiar with the concept of data batches. Very important. Equals categorical. Wonderful. So, what happens if we run this? Would you look at that? So we have 7,500 images belonging to 10 classes. That is the training data. And that lines up with what we did before with our little inspection code here. 750 images across 10 classes. What does that up to give? 7,500. And we have 2,500 images belonging to 10 classes for the test data. Does that line up with what we did before? Yes, it does. So have we become one with the data? Well, not entirely. There are a few more things we could do to inspect it, but that's enough for now. So where are we up to? Let's pre-process the data. That's That's step 3. What did we have next? Create a CNN model. So that's what we're going to have to do in the next video. Now, again, I want you to try and jump ahead of me. So we're going to go create a model. This is the next video. I'll just write this here. Start with a baseline. Now, we've been talking a lot. Let me write this down. We've been talking a lot about the CNN Explainer website. So we go CNN Explainer, one of my favorite websites in the whole world. And they work with 10 different classes. And what are we working with? We're working with 10 different classes as well. So how about we just take their model and replicate it for our problem? So yeah, how about we just take their model, also on 10 classes, and use it for our problem. So that's your little challenge before the next video, is to replicate the CNN Explainer. This is a tiny VGG architecture. You can find that, it says it somewhere on the page. But replicate this. We have an input. Our input shape is going to be different, of course. They use 64 by 64. What did we use? 224 by 224. Then we have a convolutional layer, relu, conv, relu, maxpool, conv, relu, conv, relu, maxpool, output. So that's my challenge to you before the next video, but otherwise, I will see you there and we'll create it together. How'd you go creating the model? Did you copy the one from the CNN Explainer website? What you might have noticed is it's basically a clone of Model 8, the one we created before, but this is multi-class. Actually, are we up to, what model number are we up to? Model 8? Model 7? Ah, okay. Model 7. So, yeah. The CNN Explainer website is basically a clone of this, except it uses how many convolutional layers? It uses 2 convolutional layers before a max pooling layer, whereas this went conv layer, max pool, conv layer, max pool, conv layer, max pool. So CNN is conv with relu, max pool, conv with relu, max pool, output. Okay, let's do that. So it's actually, that's a lie. It's not a direct clone of Model 7, but it's pretty close. Let's go back down here. Where were we? Far out, we've written lots of code. You should be very proud of yourself. Import, this is how we create our model. Import TensorFlow as TF. Wonderful. Of course, we've already got many of these dependencies from before, but we're going to practice writing them out again. We want the sequential, we'll turn it into a sequential model. And what layers do we need? Keras.layers. If we're going to be building a CNN model, we need conv 2D, we need max pool 2D. What else? We need a flatten layer, and we need a dense layer for the output. Wonderful. So let's go here, create our model. Very similar to previous models, but actually the same as CNN Explainer website. Except, of course, we're using different image shapes. So let's go, we're up to Model 8. I believe. If not, that's all right. We can start from Model 8. Conv 2D. What are we going to set? 10, 3, because remember, where we're getting these numbers, they're not made up. 10, and then our filter size. Where is it if we come in here? They use a 3x3 kernel. So there's their 3x3 kernel. So let's come in there. So that's our filters. We want 10 filters. We want a kernel size of 3 strides we can leave as 1, padding we can leave as valid, but what do we need? We need activation. They have a relu activation. Now I want to show you something that we could do as well. Input shape equals, just in case you wanted to separate your activation layers, let's bring in activation as well. We haven't done this before. So let's go activation equals relu. So that's if you wanted to separate it and create it exactly like they've got it here, but you could always just put in relu in here in activation. So let's go to the next layer. What do we need? We need another conv 2D. with 10 filters, a kernel size of 3, strides can stay as default, padding can stay as default. These two parameters here, but we're going to set activation equals ReLU. And then we want, what are we up to? We're up to max pool. Max pool 2D. We actually don't even have to pass anything to max pool 2D because pool size is automatically 2. That's fine by us. And then we're going to do another 2 conv 2D layers. 3 activation equals ReLU. And then another conv 2D. Activation equals trusty ReLU. And then max pool 2D. Wonderful. We need to flatten our outputs from the max pool layer, pass it into a dense layer. Oh, that was a spoiler alert. How many activation or output neurons does our dense layer have? I'll give you a hint. How many classes are we working with? We'll go 10. And then what is the activation function? So this is very important. We did a binary classification model. This is something you would have had to have changed from the binary classification model to the multi-class classification model. And what is that? It's instead of sigmoid, we use softmax. Wonderful. So this is the change. Changed to have 10 output neurons and use the softmax activation function. And again, if you really wanted to, you could delete that, and then you could write activation softmax. You could do that if you want, but we'll go here. Activation equals softmax. Wonderful. And what do we have to do after we created our model? We have to compile it. There's another thing in here that we're going to have to change from previous models. Why? Because our data is different. Compile. What's going to change? Give you a hint. It's our loss function. We used binary cross entropy before, but what data did we import? I'll give you a hint. The class mode is here. So we have to change our loss from binary cross entropy to categorical loss entropy. Categorical cross entropy. Magnificent. And then what's our optimizer? We can keep that the same. Our trusty tf.Keras optimizers .atom. And then metrics, we'll use a simple classification metric of accuracy because all of our classes are balanced and have the same amount of images in each. So compiled. Boom, look at that, created a model. We just did that. We copied a model that's out in the wild, right, using our TensorFlow skills and adapted it to our data set, which has 10 classes of images. How good is that? And I mean, if you had 100 classes of images, what would you change? Well, you might need to change this. That should be 100. And if you wanted to change your input image shape, what could you change that to? Well, it depends on what you're working with. Maybe you had 300 by 300 images. So you could change it to 300 by 300. You'd probably also have to change this, 300, 300, 300, 300. We could actually set that as a global variable, image size equals 224, 224. And then, well, actually, you don't do ... do you? That would be a syntax error. I was just doing that as I was typing. Then we could just put image size there, and yada, yada, yada. But anyway, so that's our model created. What's our next step? Let's refer back to the ones we've already done. Fit the model. All right, so now's your chance. We've got a model created, model 8. Have a go before we get to the next video. I'm going to challenge you in every video on this one, in this section, to fit the model to our new data set. So it should have 10 classes. See how you go. I'll see you in the next video. How'd you go? Did you fit our new model? Our model 8? If not, that's okay. Let's do it together. Fit a model. Wonderful. So now we've got our model compiled. Fitting it's actually quite easy. Once you've got the data ready, this is the beauty of TensorFlow. So fit the model. Of course, we're going to save our history to history8 to line up with the model number. We'll go model8.fit. What are we fitting on? The training data. So this is now 10 different classes. Probably a little bit confusing compared to the because our binary training data was also the same name, we could have maybe made this train data 10 classes to prevent ourselves from getting confused, but that's okay. We're smart enough to figure it out. So we'll go for 5 epochs, our standard amount, just so our experiments don't get too long. And the steps per epoch is that we want to tell our model to take enough steps through the training data, because remember, our training data is now in batches of 32. So we want it to take enough steps per epoch to go through every batch. And then we will go validation data equals our test data. Again, a little confusing with the variable name there, but we're smart enough to figure out what they mean. Validation steps is going to be length of the test data. Now, if you wanted it to validate a little bit quicker, we'll probably see this in a later video, but you could do something like this, 0.25 times length test data. And then, of course, you could evaluate it on the full test data set later. But that's just a little way to speed it up. So that would mean it would go through 25% of the test data to validate it while training instead of the whole test data set. So that's just one example, but let's leave that as just the full test data. And remember, if we don't know something, oh, I don't want to see my bookmarks. I need Command MB to go down there. Then train data. We write it out another cell, so 235 steps. Let's see where that number, does that come up? If we run this, you ready? 3, 2, 1, about to fit our brand new model, which is very similar to this, well, basically the exact same model as on the CNN Explainer website. Let's run it. Oh, yes. Now, I want you to pay attention to how long my model takes per epoch. If yours is taking far longer than that, remember, you may have to change the runtime type. Make sure you're using a hardware accelerated GPU, but we did that at the start of the notebook, so the GPU should be running in the background. And there we go. There's the steps per epoch. So I'm going to let mine run for however long it takes. The first epoch is generally slightly longer than the others, but I'll check back in once this model has finished fitting to the training data. All right, would you look at that? Our model looks like it's learning something, although the validation accuracy could, of course, be a little bit higher. Training accuracy is pretty good, though. It's near 75%. And so now I just wanted to do a little bit of quick arithmetic. If we're working with 10 different classes and they each have 750 images in each class, so there's no class with like 5,000 images and one with only 10 images, what would guessing be in terms of an accuracy score? 10 classes, all with the same amount of data. If we imagine 100 is the max, so 100% accuracy, which would be 1.0, and we have 10 different classes, guessing would be 0.1. So in other words, 10%, because you would just randomly guess a class in a group of 10 classes, so you could just say randomly hamburger. You could say hamburger for every image, and you'd get about 10% correct, because 10% of the images are hamburger. So our model's doing about 3 times better than guessing, but ideally we'd like to improve that. And another thing to take note here is that why do you think our model took longer to fit? Even though we're running longer to fit, that is compared to our binary classification problem, even though we're running on a GPU. So if we come back to model7.fit, how long did that take? It took about half the time. So this is 22 seconds versus what are we working with right now? Model 8, so this is about 45, 46 seconds. So yeah, about double. Well, it's because we're now working with, instead of 2 classes of 750 images, we're working with 10 classes of 750 images. And the same goes with the testing data. So that's why our model just has to simply, or our GPU just has to simply look at more examples of data to try and find patterns. That's why it takes longer. And the same would go is if we were working with 100 classes. It would take longer. The more data you have, the longer it's going to take whatever computing power you're using to find patterns in it. And so, now that we've fit a model, we've got a trained model. What's number 5? What's the next step? I'll want you to have a think about it before we check it out, but it's going to be evaluate the model. So let's write that out. That'll be the next video. Evaluate the model. So I want you to go back up, of course. This is the challenge again, to this step here that we did with our binary classification problem, and just bring the steps down here, rewrite them, but translate them to work with our multi-class classification model. I'm going to get rid of that, and I will see you in the next video. All right, this is exciting. We've trained our first model on 10 classes of food. We're getting closer and closer to building our food vision app. So let's evaluate on the test data. How might we do that? Well, we can take our trained model, model 8, and then we can just go evaluate test data. We'll probably get a very similar result to what we saw for this last epoch, but we'll check it out. Doesn't take too long. Yeah, there we go. So we get roughly, basically the exact same as we did for the output here. So this is our accuracy score, 30% accuracy. Remember, what's guessing 10 classes of evenly distributed data? It would be about 10%. So ideally, we'd like to increase this, but good news is our model is doing better than just guessing. So let's check out the model's loss curves, just like we did on the 10 classes. And then we go plot loss curves. We made this function back up somewhere in the notebook. I think it was somewhere in here, section 5, because we wanted to plot more loss curves. And we're going to pass it history equals 8. Oh, what's going on here? What do these tell us? What's the ideal position for these curves? We'd like them to line up. If our training loss is going down, we want our validation loss to go down in roughly the same manner. But we can see here, our validation loss starts to go down, but then training loss continues to go down after about the first epoch, but the validation loss just starts to explode. So what is that telling us here? It means that our model is potentially overfitting on the training data. So it's learning the training data too well and not generalizing to unseen data, which is why the validation loss just starts to explode here. And it's a similar story with accuracy. There's a big gap between the curves. Ideally, we'd like them to line up. But of course, with accuracy, we want them to go up. With loss, we want it to go down. And so, what can we do here? Let's write ourselves a little note. What do these loss curves tell us? Well, it seems our model is overfitting the training set quite badly. In other words, it's getting great results on the training data, but fails to generalize well. Remember, generalize is adapting to data it hasn't seen before, to unseen data, and performs poorly on the test data set. So what we'll probably do is we'll try to fix this, right? That's what we want to do before we're exploring too much further into evaluation. This is what I mean by experimenting. Is once you sort of get to a little bit of a knack about the experiments you should run, if you see this, well, that's something you should try and tackle as soon as possible. All you got to do is just look at this one curve and go, you know what, my model's overfitting. If I was to continue pursuing with a similar model, it's probably going to keep overfitting, so I should probably try and reduce that. So let's have a look at what our next step is. Adjust the model parameters. So what did we write for multi-class classification? Adjust different hyperparameters and improve the model. Try to beat our baseline. So we've got a baseline score, right? This is what we're going to do next. We've got a baseline score with our model we created in step 3, model 8. But we also want to reduce overfitting because our baseline is overfitting, which is, again, overfitting is not necessarily a negative thing when it's your baseline because it means your model is learning something. So let's, in the next video, let's tackle step 6, and I'll turn this into a header 3 so this looks a bit prettier. So we'll come back down into here, and we'll go here. In the next video, we're going to adjust the model hyperparameters to beat the baseline slash reduce overfitting. Now you can also refer back to the steps we took above to improve our model, or to the lecture to see how you might beat our baseline and reduce overfitting. So give that a shot. That's a challenge for this video. As I said, I'm going to challenge you at the end of each video. But otherwise, I'll see you in the next video, and we'll adjust our model's hyperparameters and see if we can beat our baseline and reduce overfitting. Welcome back. And so, what did we find out in the last video? Well, due to our model's performance on the training data, we can assume that it's learning something, but that what it's learning is not generalizing well to unseen data. That's why the validation loss is just exploding out of the roof here. So that's what we're going to try and tackle. We're going to try and improve our baseline results, and of course reduce overfitting. So bring these curves closer together. So what are some ways we can do that? So let's write ourselves a little note. We'll reiterate what we just said. So due to its performance on the training data, it's clear our model is learning something. However, it's not generalizing well to unseen data. So let's try and fix, we'll put in brackets overfitting here. Let's try and fix overfitting by, now here are some methods that we can use to prevent overfitting. So number one is get more data. Having more data gives a model more opportunity to learn diverse patterns. What's another one? We can simplify the model. So if our current model is overfitting the data, it may be too complicated of a model, which means it's got too many layers and it's actually learning the patterns too well on the training data. So the layers, the convolutional layers, maybe that means we have to take some out so that it doesn't learn as much. So that the patterns that it does learn, we force it to learn more generalizable patterns rather than specific patterns. One way to simplify a model is to reduce number of layers, or reduce, well, this is actually two ways, but it doesn't matter. We'll just, you get what I'm saying. Reduce number of hidden units in layers. What's another way we can use? We could use data augmentation. Now, I'm not pulling these out of the air, by the way. We've actually seen this here. Improving a model. This is from a data perspective. So this is a method to improve a model, reduce overfitting, more data. What does it do? But what I'm trying to do here is not always just refer back to the slides. I'm trying to get us to think about ways that we can use to improve our models without just always referencing. So we're trying to commit these things to memory, you know. Data augmentation, increase the diversity of your training data set, better data, use transfer learning. Oh, that sounds exciting. We're not actually going to cover this one. This is a spoiler for the next section. And then if we come back to improving a model from a model's perspective, if we wanted to improve our model, we could add layers, increase the number of hidden units, but this actually works in reverse when you're trying to reduce overfitting. You want to remove layers or decrease the number of hidden units. So these are the things that we've written down in the notebook so far. Use data augmentation. Data augmentation manipulates the training data in such a way to add more diversity to it, so without altering the original data. And then finally, another one, we'll put it down here for good measure, use transfer learning. Just want to give you a little spoiler and a little excitement to look forward to what we're going to do in a module coming up. Transfer learning leverages the patterns another model has learned on similar data to your own and allows you to use those patterns on your own dataset. So what can we do from these? These are some of the main ways to reduce overfitting. Get more data, can't really do that. We've got our, well, we could, but we want to sort of stay within our notebook. Simplify the model, we can do that. Yes, we can. We can remove some layers. Use data augmentation, we can do that as well. And use transfer learning, again, we could actually do that, but I'm going to save that for a future module. So, how about we try to do the simplest step first? Our simplest experiment. That's what you should keep in mind. What's the simplest experiment that you can do to get you to sort of eliminate what works and what doesn't? So let's, how about we try and simplify the model first? So what's our current model? Model 8.summary. And we've got convolution, convolution, max pool, convolution, convolution, max pool, flat and dense. I've got an idea. Let's just whack one of these convolutional layers from each of these sections. So we'll just smack 2 convolutional layers out of our model. That's a good idea. Let's try to remove 2 convolutional layers. So the ideal setup for this experiment would be, we'll simplify our model, and what do we want it to do? Ideally, we'd like it to get very similar results to this, or even better, but also we want these curves to be closer together. So they're the 2 things that we're going for. We want higher accuracy, and we want these loss curves to be very close to each other. So that's the goal of this experiment. Let's, we're up to model 9. We can code this out pretty quickly. Sequential. Now this experiment is quite simple because all we're doing is just the same model as model 8, but we're whacking 2 of the convolutional layers out. Relu equals input shape equals 224, 224, 3. Beautiful. Let's throw in a max pool and then conv 2D. This is simplifying our model. Activation equals relu and then max pool 2D. And then flatten, because we want to pass the output of max pool 2D into our dense layer as a vector. That's what flatten does. And the output is going to be softmax. How easy is that? Beautiful. Model 9.compile. We want to, what's our loss function? Too late. Categorical cross entropy, because we're working with multi-class data. The optimizer is going to be, you know this one, tf.Keras optimizers dot atom, trusty atom, and metrics equals accuracy. What just happened there? Okay, wonderful. So there's our new model. We'll go here. Let's have a look at our model 9 summary. So model 9 equals convolution, beautiful. The number of parameters didn't actually change too much. But let's just experiment and see what happens. We've removed 2 layers. Is this going to change much? There's only one way to find out, and that is to fit it. Fit the model with 2 times conv layers removed. Model 9.fit. Oh, we need our history 9, because we're saving our history variables. Train data. Epochs equals 5. Steps per epoch equals, what is it? The length of our train data. And then we can go validation data equals test data. And then validation steps equals len test data. Wonderful. Let's let this fit. Should be a little bit quicker because we've kicked out 2 layers. So I'm going to let this run through, and then, or actually, why don't we just guess now? Comparing these 2 summaries, how do you think this is going to come out? My guess is that the loss curves are actually going to be quite similar because the total number of parameters didn't actually change too much. It actually increased from model 8 to model 9. So maybe we didn't actually simplify our model too much, but again, we're experimenting here. We've got our experimenter's hat on. I'll see you once these epochs are finished, and we'll check out our model's loss curves. Alrighty, looks like my model's finished up. How did yours go? Oh, wow, we got a decrease in validation accuracy. Wow, looks like that experiment that goes down the drain. But this is an important point. Let's check out the loss curves of model 10. So plot loss curves history. Oh no, it's not model 10. We're up to model 9. I'm getting ahead of myself. Model 10 is the next one we're going to build. History 9. Wow. Okay, our validation loss curve is basically going to the moon. So, no improvement there by removing 2 convolutional layers. Why do you think that might be? The hint lies in the summary here, model 9.summary. And then can we print them both? Oh, I'll just put them both here, model 8.summary. So have a think about that. Why that might have occurred. And I'll give you a clue, it's because model 9 actually has more parameters. Even though we've removed 2 layers, what convolutional layers actually do is they reduce the feature space. So adding an extra convolutional layer here actually doesn't increase too much complexity to the model. It actually forces the model to try and learn the better features in the data. And so this is an important point though, and I wanted to showcase that not every experiment that you run will improve your results. But this is the motto of the machine learning practitioner. It's experiment, experiment, experiment. So what have we got next? What are our other options to try and fix overfitting by? We've simplified the model. Well, we've removed the number of layers, convolutional layers. We found out that doesn't really work. How about we try using data augmentation? That's something we're familiar with. So come up in here. Do we have opening our bag of tricks and finding data augmentation? Haha! So we have looked at data augmentation. How about we try that next? So we'll come down here. We'll write a little note. Looks like our simplifying the model experiment didn't work. The accuracy went down and overfitting continued. How about we try data augmentation? Yeah, that is a great idea. So let's put in here. So we go here, trying to reduce overfitting with data augmentation. So this is my challenge for you. You're going to have to create a new instance of image data generator with some data augmentation built in. So you're going to have to make a new train data variable. Maybe it's called train data augmented, something like that. And then you could even use a very similar model to what we've used before. So give that a go, create some augmented data and fit a model to it. And then a model similar to what we've built before, maybe the baseline model, and then see if that fixes our overfitting problem and increases the validation accuracy. So that's your challenge. I'll see you in the next video. How'd you go? Did you manage to create a data augmentation instance of image data generator? Did it work better than our simplifying the model experiment? If you haven't tried it just yet, that's all right. Let's write ourselves a note of what we're going to do in this video. Let's try and improve our model's results by using augmented training data. Ideally, we want to reduce overfitting, get the train and validation loss curves closer. And the next point is we want to improve validation accuracy. So this is what we want. This is what we want to do. How can we do it? We need to first create an augmented data. That's a fun word, isn't it? Augmented. Instance, it sounds fancy. We want train data gen. We're going to call it augmented. Oh, we've already gotten this variable. Again, we could name it something better, but this is just for simplicity. We want to go image data generator equals rescale 1 divided by 255. And then what can we do to augment our data? Let's come back to our keynote. And we want our data augmentation options. So here's what our original images look like. We could rotate them, we could shift them, we could zoom them. And the good thing is that TensorFlow has a bunch of these methods built in for us. So let's just go wild and do a combination of a bunch of different ones. So maybe we'll rotation we'll use rotation range. Where is this one? Rotation range equals 0.2. Width shift. Height shift range equals 0.2. Zoom range, we'll zoom in on it as well, 0.2. And then a horizontal flip, why not? We'll flip around the horizontal axis equals true. Wonderful. Okay. So there's our augmented data generator instance. And then we can, oh, we don't want to do that. We want to train data augmented. Thank you for the autofill. Train data augmented data gen. Now, of course, shuffle is going to be true here by default. Where's shuffle? Is shuffle in here? Anyway, shuffle's on by default, so that's why we don't have to put in shuffle there. Train data augmented. We're going to pass it our training directory. Target size is, we know this one by now, 224 by 224. Again, you could adjust that depending on your use case. Batch size, same thing. You could adjust this depending on your use case. And then class mode is going to be categorical. Wonderful. So, what do we have here? Oh, we need to flow from directory. Of course we do. Let's bring this out there. Bring that one out there. Make our code look nice and neat, like the Pythonistas that we are. Wonderful. We have 7,500 images belonging to 10 classes, but now we have an augmented version of our data. So, what can we do? Well, we can create another model. So let's create another model, but this time we'll fit it on the augmented training data of 10 classes. Does that sentence make sense? Sort of. I believe we're up to model 10. So model 10, I want to introduce to you, so this is one way we're going to cheat. We're not going to rewrite all of our model code. We're going to clone model 8. You might be able to infer what this does. So model 8, let's remind ourselves of what model 8 is. Model 8 is the same as the tiny VGG architecture. So we're going to clone that, but the clone model function, if we come back down to here, clones just the model architecture. It doesn't clone any of the things that, because what? Model 8 has already learned some patterns. But clone model copies the model without any, it resets all of its internally learned patterns. So if we get the doc string here, clone any model instance. Model cloning is similar to calling a model on new inputs, except that it creates new layers and thus new weights instead of sharing weights of the existing layers. That's a key point there. So that's just model 10. We're creating the same as our baseline, except what are we trying to do with our experiments? We're trying to beat our baseline. So model 10 is a replica of our baseline. However, the experiment we're running is fitting our baseline on different data to try and improve the loss curves and increase the validation accuracy. That was a mouthful, but we are going to compile the cloned model using the same setup as previous models. So we've done this a few times now. So model 10.compile, and we want loss equals categorical cross entropy. Entropy. And then the optimizer is going to be, of course, our trusty optimizer atom. Optimizers.atom. And then finally, the metrics is going to be accuracy. Wonderful. Now, before we fit this, let's just do a little comparison just to see if I'm not a liar with model 10 being a clone of model 8. 8.summary. Fingers crossed, I'm not a Pinocchio. There we go. So there's the total parameters. There we go. How cool is that? Just a little clone model feature. If you ever see that, that's what clone model does. It takes the architecture of the model you pass it, but it resets all of the internally learned patterns. Let's get rid of those. Now we've got a compiled model. What can we do? We can fit the model. That's going to be history 10 equals model 10.fit. And then what do we need to change here? We need to fit it on the training data augmented. Yes, we do. Epochs is going to equal 5, and then everything else will stay the same. Steps per epoch. That can actually be the length of the trained data augmented. And then we will also set up the validation data to equal the test data. And then finally, the validation steps equals the length of the test data as well. Wonderful. Are you ready? You ready to fit a model? What's going to happen actually? Do you remember when we fit our other model on augmented data, what happened to the length of how long did each epoch take? Did it increase? Did it take longer? What do you think is going to happen here? You ready? Let's find out. 3, 2, 1, run. Beautiful. Oh, we can see that the ETA has increased quite a little bit from what we had before. What did we have before for the first epoch? 43 seconds. Now, why is that? Well, it's because we're using augmented data. And remember, this function here, image data generator, augments data on the fly, so as it's been loaded into the model. So that means that all of our data here remains unchanged. So it just augments the data while it's loading in, hence why the epochs take a little bit longer, because it takes a bit more compute power to augment that data. But I'm going to let this run for however long it takes to run, and then once it's finished, we'll come back and we'll check out the loss curves of our model fitting on augmented data and see if it also improves the validation accuracy from our baseline. I'll see you soon. All right, looks like the model's finished, training on some augmented data. And you can see it takes a fairly long time compared to our model trained on non-augmented data. About double the amount of time. That's because, as we said, when the data gets loaded in, it gets augmented on the CPU, and then the data gets loaded onto the GPU, hence increasing the amount of time per epoch. But let's have a look. Oh, we'll peek at our validation accuracy. It's increased a little bit. That is beautiful. What were the results on our Model 8, our baseline? So evaluate test data. Let's remind ourselves of that. And then we can do the same here. Model 10 dot evaluate test data. And then, of course, we want to check out our model trained on augmented data's loss curves, because that was the other thing we wanted to improve. We'll go plot loss curves, history underscore 10. Oh, that is looking much better. All right, so let's first step through this. We see here, this was Model 8, our baseline, trained on non-augmented data. Same architecture for Model 10, remember, because we've used clone model. But training on augmented data, we've seen an increase in validation accuracy of almost 10 percentage points. That is incredible. And even better, the training loss and the validation curves are heading in the right direction. It even looks like if we were to keep our model training for longer, this would keep decreasing and accuracy would keep increasing, of course. This curve is not perfect, but it's a lot better than what we had before. It's certainly heading in the right direction compared to, if we had a look at here, our original one, plot loss curves, history 8. Certainly looking a lot better than that. I mean, that was exploding up to the top. At least our validation loss curve for Model 10 is heading downwards. So let's X out of that. So we'll write a little note here. Whoa, that looks much better. The loss curves are much closer to each other than the baseline model, and they look like they're heading in the right direction. Certainly not the wrong direction. So if we were to train for longer, we might see further improvements. That might be another experiment that you can run. But where are we up to? So we've covered a few experiments here so far, simplifying the model. What did we do next? So we adjust the model parameters there, we checked out our bag of tricks data augmentation, and we repeated until satisfied. Okay, so I think that's the next one we'll go through. So I'll leave this here. Repeat until satisfied. This will probably be a short lecture actually. We'll just discuss some of the things that we could try. But my challenge to you is to write some of them down. Out of all the things that we've tried so far, what could we try? This is a little hint here. But I won't reveal anything until the next video. So have a go at writing down some things we could do to further improve our model, and we'll discuss them in the next video. We're up to step 7, repeat until satisfied. Now, just have a look at what you've done here so far. We started with a binary classification problem, we broke it down, and then what we've done is we've applied all of those steps we did with our binary classification to our multi-class image classification problem. And so, we can write here, what are some steps we could do? Well, we could keep going here, continually trying to bring our loss curves closer together and trying to improve the validation / test accuracy. How? By running lots of experiments. Namely, we could try restructuring our model's architecture, e.g. increasing layers / hidden units, or in the convolutional case, we could increase the number of filters. We could adjust learning rate, but it does seem like our model is learning pretty good already with the default atom learning rate. We could try different methods of data augmentation. And what I mean by that is adjust the hyperparameters in our image data generator instance. So that would be up here, where we created our augmented data. We could play around with some of these to see if different values lead to improved results. What else could we do? We could try training for longer, e.g. 10 epochs instead of 5 epochs. Most of these things we've kind of talked through, right? We've got improving a model from a model's perspective. We could add layers, increase the number of hidden units, change the activation functions, change the optimization function. So Atom works pretty good, but maybe we want to try something else. Change the learning rate, fit on more data. So we could find some more data somewhere online, or we could collect it ourselves. And we could try to fit for longer. But there's another way we haven't quite looked at yet. So we've discussed more data. This is from a data perspective this time. We've discussed data augmentation. We've discussed better data. But how about using transfer learning? So take an existing model's pre-learned patterns from one problem and tweak them to suit it for our own problem. For example, take a model trained on pictures of cars to recognize pictures of trucks. So we'll put that one down here and then try transfer learning. Now, we're not actually going to go through that in this module. That's going to come up. It's actually going to be quite a large section of this course, transfer learning. But if you want to have a look into, you could run a bunch of experiments such as these ones we've just discussed here. But if you want to sort of go ahead and do some research on what transfer learning is, well, that's what we're going to do in the next module. We're going to see what transfer learning is and how we can use that to improve our model's results. But the goal here with repeating until satisfied is that what we're trying to do is, of course, make our loss curves better and then improve whatever our target metric is. So in our case, it's validation accuracy. So that's what step 7 would be in a nutshell. That's a nice and short little text-based lecture. We didn't actually write any code. But now, since we've got a trained model, let's make a prediction with it. Making a prediction with our trained model. More specifically, we've seen how our model does on the test data set. So the test images. How about we get some of our own custom images from the 10 food classes? Remind ourselves what class names is. We'll find some of our own images based on these classes and see what our model does. So I'll meet you in the next video. If you want to give it a shot, you can try to upload some of your own data here. Try to upload something that, if you've got a photo of a chicken curry you've cooked, or maybe you're really good at making homemade pizza, upload that to Google Colab, and we'll write some functionality or some code to make predictions on those images. All right, time to take down one of the most exciting parts of machine learning, and that's making a prediction with our trained model on, let me write in here, write ourselves a little note. Let's use our trained model to make some predictions on our own custom images. And then we've got our little reminder, remind ourselves of the classes our model is trained on. So we've got the class names there. And what do we need? If we're going to make some predictions on custom images, what do we need? Well, we need custom images. So what we're going to do is download some custom images. So I'm going to go to the course GitHub. I've uploaded some images already. And so we'll get the classic pizza dad. How about, what else could we get? We get the hamburger. Let's get sushi. And let's also get steak.jpg. And now we need the raw version of this. So you need to click the download button. We're going to copy that URL. And we're going to go wget, copy that in there. That's pizza dad. The same thing with this one. This is the hamburger. So we're going to copy that. wget. And then the same thing for sushi.jpg. And we're going to go right, wget. Wonderful. And then finally, we need steak.jpg. Oh, I am such a good chef. Wget. Boom. So this is all going to download. And we'll just clean up our browser tabs there. Of course, if you don't want to download the ones from GitHub, you could just click the little upload button here. And you can upload your images to there. And it will... Oh, wow, we've got a fair few copies of Pizza Dad. And it'll upload it to the Google Colab session. Remember, when Google Colab disconnects, all of these will be deleted. So if you don't want to lose your work, make sure you've got it somewhere else that's not Google Colab. So we should have some images. And we've got a function we made before. Let's see if it works. So make a prediction using, what's our current model? We're up to model 10? I think we are. Model 8, model 10. There we go. Make a prediction using model 10. So we've got a function we created before called pred and plot, which takes in a model 10. It also takes in a file name. Which one should we do first? Well, we downloaded Pizza Dad first, so we'll just copy this path here. 03, file name. And now, of course, you can change this to whatever you want, whatever your custom image is. I'm just using Pizza Dad. And then the class names is, of course, the class names variable. Let's see if this function works. Oh no, what's it got wrong here? Only one size arrays can be Python scalars. What have we got going on here? So class names. So there's the error. Class names. Ah, that's an array. Maybe if we pass it in as a list, it should work. List. All right, let's see if this works. List. It didn't work. I think there might be something up with the image, maybe. All right, let's check our pred and plot function. Def pred and plot. Class names int round tf pred passes it in load and prep image file name. Yes. Class names equals class names. You know what? It's our pred and plot function is set up to only work with, I think that's what's going on. Is it only works with, that's what's happened. It only works with binary images. So we need to adjust it to work with, let's bring this down here. We need to adjust it to work with multi-class images. So this is where our error is. So reconfig pred and plot function to work with multi-class images. So how can we do this? So there's the pred and plot function. I think we need to, the prediction. So if we go print pred, is this going to work? Does it print anything? Okay, there we go. I think that's where it is. Only one size arrays can be converted to Python scalars. So it comes out like this. We actually want it to be, so the predict I think can stay, but then we need to add in, how can we do this? We need to add in logic for multiclass. So if the length of pred 0, because we want to 0 index it, because look what came out like that. We only want this inner array here. If length of pred is greater than 1, because remember, if it's a binary class classification, it's only going to, the sigmoid function is only going to output one number, but the softmax activation function outputs prediction probability for every class that our model is trained on. So if pred is longer than 1, which means it's multi-class, we want to go pred class equals class names pred dot or tf dot argmax. So get the position in here which has the highest value. So in this case it would be, where is it? This class, whatever index that is, argmax pred. Wonderful. And then else, so this is for binary classification, else it would just be this. Yeah, that's correct. Add in logic for multi-class and get pred class name. All right. So I think this should work. If in doubt, run the code. What do we got here? Only integer scalar arrays. Maybe we get rid of that list. This is some live troubleshooting here. How fun is this? Okay. Too many indices for array is one-dimensional, but 10 were indexed. tf argmax. If length pred print pred. This is how I troubleshoot functions. Print pred len pred 0. 10. Wonderful. So class names, yes, if pred 0 is 10, if it's longer than 1, yes, pred class equals. Now this is what we also need to print. We need to print tf argmax pred. That's also what we need. Shape equals 10. Oh, we need to index on 0 here. Oopsies. What happens there? Oh, there we go. Boom, have a go at that. All right, this is predicting the wrong class, ramen. We need to get rid of that, these two outputs. That might have broken that for binary classification, but I'll let you check into that. Let's run this again. Okay, so I got that one wrong. Let's try another one of our images. What do we have? Steak.jpg. Grilled salmon. So I got that wrong. Didn't get any of them right. Oh. No. Oh, sushi. Sushi.jpg. Grilled salmon. Okay, you can kind of understand why it might be picking grilled salmon there. And then let's try, finally, hamburger. Sushi. All right. So it looks like our model is performing pretty poorly. Like it didn't get any of those correct. So that's probably where we'd be looking to definitely improve it before we deployed this into our food vision application. So before we move forward onto the next module, and we'll see how we can actually improve our model, let's save it just so we cover all bases. So we'll see how we can save and load our trained model. I'll see you in the next video. Welcome back. Just a little update on our updated pred and plot function. It does work with binary classification. So if we bring in model 3, which was trained on binary classification, let me just write a note here, trained on pizza versus steak, and we pass it the file name pizzadad.jpg, pass it the class names as a list, pizza and steak. We run it. Wonderful. And then, why not for good measure, we try it on the steak. Steak. Beautiful. So, just a note here as well, our model didn't do very well on our own custom data, which is kind of not the highest note to sort of finish on, but that's all right. We're going to see how we can improve this out of this world in the next module. But let me just write a note here. Looks like our model didn't perform very well on our custom images. But this is because, so we were kind of expecting this. This is because it only achieved 39-ish% accuracy on the test data. So we can expect it to function quite poorly on other unseen data. But that's all right. We'll see how we can improve that in the next module. But we said at the end of the last video that we're going to save and load our model. So saving and loading our model. This is important for if you wanted to, say, deploy your trained model, such as Model 3, which works a bit better on pizza and steak, or if you actually did want to try this out, Model 10, in some sort of application. You could save it to a TensorFlow saved model, upload that to Google Storage or something like that, host it on Google's AI platform, and then deploy it as an API. Of course, there's a lot of words that I just said that we haven't covered, but this is just so that you know how to save your trained models. And let's go here. This is how we save a model. And let's say our target model is 10, save, and then we want to save it as saved trained model 10. And then we can just run that. This is going to appear, save trained model 10. The default is in the saved model format in TensorFlow. So there we go. And then if we wanted to, we can load in a trained model and evaluate it. This is just so you know, we've saved it here. It's going to save the model, all the weights, all the patterns, etc., etc. To make sure that it's saved correctly, we can go loaded model 10 equals tf.models.load model, and then we go saved trained model 10. And then we want, oh, we need that bracket back up there. Then we want loaded model 10. We're going to evaluate that on the test data. Shift and enter. All right, so we'll see how it performs there. And then we can go here, compare our loaded model to our existing model. So model 10.evaluate test data. So these should be the exact same results. If our model has been saved correctly, reloaded back in, we've evaluated the loaded model, and this is the model we originally saved. There we go. Look at that. Beautiful. Same results. Slightly different at the back end of these numbers here. Again, that is because of how computers store numbers. They aren't quite exact, so once you get really close to the tail end, you might see a little bit of differentiation. But for the first half a dozen decimal points, we've got the numbers lining up. Well, that is very exciting. Look how much you've covered. Introduction to convolutional neural networks and computer vision with TensorFlow. We started with an end-to-end example. Went through that like an absolute whirlwind. And then we broke it down step by step with binary classification. We became one with the data. We pre-processed our data. We created a CNN model. We actually learned what a CNN actually is. We learned what a convolutional layer is. We learned what kind of layers and what kind of things comprise a convolutional layer. We had a look at our favorite website for convolutional neural networks, the CNN Explainer website. There's definitely a lot to take in, but that's like with learning anything new, anything worthwhile, there's a lot to take in. So I'll let you read through that again. We fit the model, we evaluated it, then we did it all over again with multi-class image classification. However, we kind of finished on a model that didn't do too well on our custom data. Sad face. But that is all right. In the next module, we're going to see how we can improve a score like this using the power of, did we mention it up here? This is a spoiler for the next section, by the way, transfer learning. So, once you finish this video, I'm going to attach some extra curriculum and some exercises to practice what you've learned all throughout this module. So have a go at doing those first. Make sure you try and do them yourself before looking at any kind of solutions. And then, yeah, I'll see you in the next module. Oh, and PS, the extra curriculum and exercise will be linked after this video. However, if you want to find them, don't forget, we've got the GitHub. You can go to TensorFlow Deep Learning, and then this beautiful table will take you to everything you need to know. So go to exercises, boom, there we go. 03, computer vision and convolutional neural networks and TensorFlow exercises. So, number 1, spend 20 minutes reading and interacting with the CNN Explainer website. You might have already done that. But congratulations, massive effort on making your way through section 3. I'm not sure what this section is going to be called on wherever you're watching this, but it is third notebook that we've gone, and you've written a lot of model code specifically to do with computer vision and TensorFlow. Give yourselves a pat on the back. I'm very, very, very proud of you, and I will see you in the next module. Transfer learning with TensorFlow. I told you I'm going to do that at the start of every new module. And now I am so excited for this upcoming series of videos. It's actually going to be possibly the next 3 notebooks at least. We're going to be covering one of the most powerful techniques in deep learning, and that is transfer learning with our friend TensorFlow. And this is part 1. So transfer learning, there's a few different types of it. We're going to cover, in this section, we're going to cover feature extraction. Now again, you've probably never heard of transfer learning, or maybe you have, and you've probably never heard of feature extraction. Well, if you haven't heard of transfer learning, you've probably never heard of feature extraction either. But we're going to start to cover these topics, so don't worry. However, first and foremost, where can you get help if you run into a problem with this section? And just to remind you, it's normal to run into errors with your code. You might see me writing code and not running into errors, but trust me, to get to that point, I went through lots and lots of errors. So first and foremost, follow along with the code if you can. Remember our motto, if in doubt, run the code. Try it for yourself, write the same code as me, run it, see what happens, what are the outputs. If I'm writing a function and you're not sure what's going on with the function, write it out line by line and see what happens there. Press Shift, Command, and Space if you're in Google Colab to read the doc string. That'll give you information about the functions that we're running. If you're still stuck, you can try searching for it. You'll come across resources such as Stack Overflow and the TensorFlow documentation. Now, the TensorFlow documentation is quite verbose, but with some practice, and by verbose, I mean there's a lot going on, but with some practice, you will definitely start to work your way around that. Once you've done that, try again. If in doubt, run the code, and then finally ask. So don't forget the Discord chat, and yes, that includes the inverted commas. I'm putting my fingers up in the air, you can't see me, but including the dumb questions. There really are no dumb questions. If you've gone through these steps and you're still stuck, there's no such thing as a dumb question. So let's get on to it. You're probably asking, what is transfer learning? And that is a great question. And what you may have thought in the previous modules is that we spent a lot of time constructing our neural networks, right? But you may have thought, surely someone has spent the time crafting the right model for the job. And that's the exact premise of transfer learning, is that chances are, depending on what problem you're working on, someone has probably already created some sort of neural network that works at least somewhat with the problem that you're working on. And we're going to get very hands-on with this throughout this. So the slides are conceptual, but we're going to see this in TensorFlow code shortly. Now, this is some example transfer learning use cases. We've covered computer vision. We did that in the last module. So one example of transfer learning in computer vision is there's a very popular computer vision data set called ImageNet. We're not going to go into that, but you can imagine ImageNet as just millions of different images of a whole bunch of different things. We've looked at food images so far. We've seen that slowly working towards building our food vision app. ImageNet is of food, of cars, of animals, of plants, you name it, it's probably an ImageNet. So a lot of computer vision research around deep learning for computer vision, ImageNet is used as a benchmark. So what that means, someone will spend a while crafting a computer vision architecture, much like the CNN architectures we've spent time building, and they will try to get the highest possible score on ImageNet. And so the better the computer vision model, the higher the score. At least that's the goal, right? And so, if someone is spending all of this time building computer vision models to do really well on ImageNet, how come we can't leverage that for our own problems? I mean, take their existing computer vision architecture and apply it to our food vision problem. Well, guess what? We can, and we're going to see how we can do that. We're going to see how we can leverage state-of-the-art computer vision architectures trained on ImageNet, and then adapt them to our use case. That's the whole premise of transfer learning. It's taking what one model has learned in a similar domain to ours, in our case, classifying images, and then it's applying it to our specific use case. So where ImageNet might have 1,000 different classes of images, our food vision application, we might only have 10 different classes of food, or in this case, there's 3 different classes of food here. And what you'll see is that transfer learning, we can get amazing results in far less time and far less handcrafting our own architectures because, again, we're leveraging the hard work of others. And so, it can also be used in problems such as natural language processing. In other words, finding patterns in textual data. So you can imagine a neural network trained to find patterns in text. We haven't covered natural language processing yet, but it's very similar. The premise is very similar to what we've done with image classification. With natural language processing, you turn text into tensors of numbers. You build a NLP architecture to find patterns in those tensors of numbers, and then you use those for whatever your use case is. So for example, you could imagine there's a neural network architecture somewhere out there trained on all of Wikipedia. So it understands which words should come in which order. And then we could probably adapt that already trained architecture to our problem of classifying whether or not an email was not spam or spam in this case. Look, I really wish this email wasn't spam. I mean, that's a large sum of money, but hey, if it's not coming into my inbox because we've leveraged a neural network to make sure that this phishing link doesn't come into my inbox, well then I'm happy. And so the premise of transfer learning is a model, a deep learning neural network architecture of some kind, learns patterns/weights from a similar problem space. For computer vision, it might be on ImageNet. Or for natural language processing, it might be on all of the text on Wikipedia, so just a large amount of text. So it learns the patterns from a similar problem space. And then in our case, where we want to use it, we want to use the patterns on our specific problems. So for the case of food vision, it would be classifying different images of food. And for the case of deciphering whether an email was not spam or spam, we might use it there for natural language processing. And so, if that's the use cases, why would we use transfer learning? And now you might have already intuitively, we've kind of hinted at this already, but just to make it clear, we've got a slide for it. So transfer learning, why use it? We can leverage an existing neural network architecture proven to work. So that's the important point. Instead of doing a whole bunch of experimentations, writing our own models for hours and hours, even days, even weeks on end, we can find something that other people have found that works on their problems that are similar to ours, so we can use that. And instead of waiting for our own handcrafted neural networks to train on a large amount of data, we can leverage a working architecture, so one that's proven to work, which has already learned patterns on similar data to our own. So this often results in great results with less data. And again, this is just text on a slide, so pretty boring. We're going to see this hands-on with code very shortly. So here's the example. We'll rediscuss this again. So for computer vision, it may learn patterns in a wide variety of images, such as using ImageNet. Researchers may have discovered an efficient net architecture. Efficient net is one of the state-of-the-art computer vision architectures at the moment. Now again, this is an important point. The architecture, EfficientNet, is currently proven to work. However, this may change over time, but that's the beautiful thing about transfer learning, is that once a new state-of-the-art architecture has been discovered, it's usually best practice, depending on what your problem is to use the architecture which is performing best in your problem domain. Okay, so in our case, at the time of recording this, EfficientNet is one of the best at identifying patterns and images. So it already works really well on computer vision tasks. What we're going to look at doing is tuning those pre-trained architecture, so leveraging those already learned patterns from ImageNet to our own problem. In our case, it's building this food vision app. And so our model, well, this is just text on a slide. I'm going to back up my claims with code in a minute. Our model performs better than if we just trained it from scratch because we're leveraging patterns already learned. So these are the main two reasons of using transfer learning. But again, it's just text on a slide. Let's go through what we're going to cover and then we'll get into code. So this is broadly. So we're going to introduce transfer learning with TensorFlow. We've talked about it conceptually, but we're going to get hands-on with code. We're going to use a small data set to experiment faster. 10% of training samples, so the exact same data set we used in the last module for computer vision. We're going to build a transfer learning feature extraction model with TensorFlow Hub. We haven't discussed what any of this is yet, but don't worry, we will. We're going to use TensorBoard, we haven't seen that again, to track modeling experiments and results. And how? Well, we're very familiar with this little diagram. We're going to do it as cooks. In other words, we're going to be cooking up lots of code. So cooks, not chemists, lots of experiments. You ready? Well, let's code. Hold on. This quote is actually perfect timing. Do the best you can until you know better. Then when you know better, do better. So far we've been building our own computer vision architectures, and they've been the best that we've known. But now we're going to be introduced to transfer learning. And so when you know better, do better. Oh, I'm so excited for this. Let's open up our good old friend, Colab. Is it colab.research.google.com? I should know this off by heart already. I usually just go to Colab. Beautiful. We're going to start a new notebook. And we're going to call this 04. Let's go transfer learning in TensorFlow. And part 1, feature extraction. And I'm going to put the video tag on the end of mine because this is the notebook to go along with the video. Just a little reminder that if you go to github.com/mrdbourke/TensorFlow deep learning, all the course materials are here. Hey, it's even got the little course materials there. So if you want the original notebook, there's a table here in the TensorFlow Deep Learning GitHub, the repo. The original notebook will be here, so that'll be the ground truth of all the stuff that we're going to go through, and I'll also add this once we're done to the GitHub. So make sure you bookmark that, and that way you'll be able to access all the resources for the course. And so let's call this one, we'll give it a little heading. We'll go transfer learning with TensorFlow part 1, feature extraction. And we'll just remind ourselves of what transfer learning is. So transfer learning is leveraging a working model's existing architecture and learned patterns for our own problem. And so there are 2 main benefits. What are they? Can you remember from the last slide? We're not going to go back to it. We're just going to try and remember these. So number 1 is can leverage an existing neural network architecture proven to work on problems similar to our own. This is very important. And number 2 is can leverage a working neural network architecture which has already learned patterns on similar data to our own. Then we can adapt those patterns to our own data. Okay, so that's a fair amount of text to start off with, but this is just so we know what we're covering. And so in this video, what do we have to do first whenever we start with a new problem? Well, in the steps for modeling, you might have remembered we need to download and become one with the data. So how about we do that? We've kind of, I've got a typo here, transfer learning. But before we do that, we need a GPU for this. So come into runtime, change runtime type. I'm going to change mine to GPU. So that's going to speed up all of the neural network code that we run. Finding patterns and numbers, a GPU is much faster than no GPU. So I'll click save on there. And then we'll make sure that our runtime is connected. And we can check, are we using a GPU running NVIDIA SMI? And beautiful. We've got a Tesla T4 GPU. Excellent. That'll be plenty enough for what we need. So how about, let's start off. We'll get some data in here. Download and becoming one with the data. So as I said, we're kind of going to go a little bit faster with some of the sections that we've already covered. We're using the same data set as we used in the previous notebook. So 10 food classes, all data. We're using the same one here. But this time, actually, we're using 10% of it. This is where the power of transfer learning is really going to shine. So in our previous notebook, we used 10 food classes, all of the data. So there were 750 images in each class. Now there's only going to be 75 images for each training class. We'll see this when we explore the data. So let's get data, 10% of 10 food classes from food 101. And we are going to import zip file. And then we can download the data, which is stored on Google Storage. So I'm going to come in here, copy that link address. Again, this is from this link here. All the links will be where you need to find links. wget. Here we go. We're going to do that. And then we will unzip the downloaded file. So we want zipref equals zipfile dot zipfile. And then we need to pass it the path to the downloaded file. 10 food classes, 10% dot zip. Beautiful. And then zipref dot extract all. And then zipref dot close. So this shouldn't take too long at all. Downloading from Google Storage. Beautiful. And now, do you remember how we walked through all the different directories within the file we just downloaded? Here we go. 10 food classes, 10%. So if you remember from the previous module, we had training. We have 10 different classes from the food 101 data set, which is just this one on Kaggle. I'm just going to link this here. I've just downloaded this, pre-processed 10 classes and chosen 10% of those randomly selected training images from each class. I'll leave the pre-processing notebook where you need links as well. Boom. All right. But instead of just talking about it, let's inspect our data. So how many images in each folder? We can do this by importing OS, and then we can walk through 10% data directory and list number of files. So for dir path, dir names, file names, in os.walk, we want 10 food classes, 10%, and then we want to print we want len of dir names, directories, and len file names. So this is inspecting our data, very important step with each new project in dir path. So this is going to output what is in our data. Let's see what this says. Okay, so there are 2 directories and 0 images in 10 food classes, 10%. Wonderful. And there are 10 directories and 0 images in 10 food classes, 10% test. So there's 250 images in each of the testing classes. So the test data is actually the same testing data that we used in the previous module in Notebook 03. And the only difference here is that instead of 750 images in each training class, we're now using 75 images in each training class. Now, this is going to highlight one of the powerful features of transfer learning. So we've only got 10% of the training data that we had before. So 10 times less examples for our model to learn. Intuitively, how do you think this will go? If our model had 750 examples of what fried rice looks like, do you think it would do better than if it had 75 examples? So intuitively, you might think that less data leads to worse results. And that would make sense of all the things that we've learned for deep learning so far. But as we'll see shortly, transfer learning has another idea. So what you could do if you wanted to is visualize some of these, but it's the exact same data we've used in the previous module. So I'll let you write a little function here to visualize what the images are going on. But let's create, because we're working with TensorFlow, we're going to create some data loaders. So this is preparing, I forgot how to spell for a second, preparing the data. So we'll use the image data generator class to load in our images in batches. So maybe I'll turn that into Markdown so we don't get an error. And we'll go here, set up data inputs. So from TensorFlow.keras.preprocessing.image import image data generator. Now there's nothing in this cell that we haven't seen before, except this time, actually that's probably a little lie. We're going to set up a global variable this time, so we're not typing them out all the time. Now in deep learning, you'll see a lot of notebooks that write things in capital letters. This is just something you'll come across. I just thought of it then. And that usually means that this is some sort of hyperparameter. All right, so if you ever see a capitals in a deep learning example notebook, generally that's a hyperparameter that's going to be used somewhere else. So we could do epochs equals 5. We're going to set that later. And we're going to go train dir. What's our training directory? Well, it's 10 food classes. This time it's 10%. 10% of the training data. So 10 times less data than what we used in our previous notebook. Train. Oh, we need to get rid of that. And the test dir is going to be, my fingers are not dancing around the keyboard how I want them today. Test, wonderful. Now, what do? We need to set up a train data gen. So we'll go image data generator. We need to rescale our data, 1 divided by 255 dot. Beautiful. And then we're going to do a test data gen equals image data generator. Same thing here, rescale, 255 dot. And then we're going to print out training images. And we can go train data 10%, just so we know that we're using 10% of the training data. Train data gen flow from directory. And we're going to pass it train dir. And then the target size can be our image shape that we created up here. So we'll go image shape. And then the batch size can be, you might have guessed this, can be the batch size. And then the class mode is what? What type of data are we working with when we've got multiple classes? I've kind of spoiler alerted it there, but that's all right. We're working with categorical data. If we were working with only 2 classes, what would it be? Binary data. So now let's print out the testing images. And we want to go test data. Now, the test data is the exact same test set we were using in the previous notebook. So although there are less training images, there's the exact same testing images, the same amount and the same actual images in the testing directory. So that's all you need to know for that. We're going to go test data gen. That way we can compare the results of our transfer learning model that we're about to build with the results of the models we built from scratch in our previous notebook. Batch size is going to be batch size, and then class mode equals categorical. Alrighty, so let's load that. Oh, image shape is not defined. Oh, I actually typed it fully out to be image. I've tried to reduce my number of keystrokes and ended up not. Okay, wonderful. So, this is good timing for this warning. If you're using a GPU, because Colab gives you free resources, and this actually costs Google money, so if we've set up our runtime to use a GPU, Colab will intermittently tell you, hey, you're using a GPU, but you're not using the GPU. So do you want to stop using that GPU and give it back to someone else? So if you're not using a GPU, it's very kind to just let someone else use that, but we're going to be using one very shortly, so it's safe to ignore that warning. So as you see here, We have training images. So this time we've only found 750 images belonging to 10 classes. So instead of 7,500 images, we have 750, but we have the exact same amount of testing images. So this is a very important point to showcase the power of transfer learning. We have 10 times less examples for our model to learn patterns on. So just keep that in mind as we go forward. In the next video, we're going to set up something new that we actually haven't seen before. So get ready for that. I told you this is a very exciting module. Taking over or learning some of the most powerful concepts in deep learning. I'm so excited. I'll see you soon. Now, before we build a model, there's an important concept we're going to cover. Well, we're going to get very familiar with it actually, because it's going to play a key role in our future model building experiments, and that is callbacks. So let's write a heading here, setting up callbacks. Now, callbacks are things to run whilst our model trains. All right, let's break this down. So I'm going to write it in one sentence here. Callbacks are extra functionality you can add to your models to be performed during or after training. I know I've said while our model trains, but they can also happen after training. Now, let's talk about some of the most popular callbacks. So some of the most popular callbacks are, again, these are just going to be the names. We're going to look at the explanation. We're going to get hands-on with them first. So tracking experiments with the TensorBoard callback, model checkpointing with the model checkpoint callback, and stopping a model from training before it trains too long and overfits with the early stopping callback. Now, we've said 3 there. These are some of the most popular callbacks because they're very helpful. We're going to get hands-on experience with all of them eventually, but I just wanted to say the names of them now so that when I mention them later, it's not like, whoa, where did this come from? So let's have a look. Let's go TensorFlow callbacks. We've only mentioned 3, but there's a lot. So we come in here. You can even write your own. Look at that. So we're going to use some of the pre-existing ones. This is the TensorFlow documentation in the tf.Variable callback. So abstract base class to use to build new callbacks. So writing your own callbacks. But here we have, where's the overview? Overview. Callbacks. Callbacks. Utilities called at certain points during model training. Beautiful. Then we got a few other options. So these are all the existing ones. Early stopping, there's the one we talked about there. Learning rate scheduler, that's something that will change your learning rate as you go. Model checkpoint, that'll save the Keras model or model weights at some frequency. So say, for example, we wanted to save our model every epoch instead of at the end of training, we could use the model checkpoint. And then TensorBoard, enable visualizations for TensorBoard. We'll see what that is shortly. So let's go back to the keynote. What are callbacks? Callbacks are a tool which can add helpful functionality to your models during training, evaluation, or inference. And some popular callbacks include, we've discussed these 3, callback name, TensorBoard, use case, log the performance of multiple models, and then view and compare these models in a visual way on TensorBoard, a dashboard for inspecting neural network parameters. This is helpful to compare the results of different models on your data. We can use that with the code here. There's model checkpointing. We've discussed what that can offer. And there's early stopping. But again, this is just a slide. And if you're like me, you like to learn things by writing code. So how about we create a TensorBoard callback? All right, we'll go back to our notebook. And why would this be important? Why would we want to track our experiments? So how have we done it in the past? Like in our previous notebook, if we open another Colab tab and we go to notebook 03 here, we kind of didn't even track our experiments, did we? We just scrolled up and down the notebook looking for different model results. So here's what we did. We were like, okay, where's one model? There's a model. That's what it got, validation accuracy. All right. Did it beat it on this one? No, it didn't beat it. How about on the next one? Oh, I beat it on that one. And then everything's all over the place. So this is where the TensorBoard callback is going to help us. Again, TensorBoard covers a lot more things than just experiment tracking, but we're going to use it to see what experiment tracking looks like in TensorBoard. So where we go, we got another model. Yeah, all over the place. All right, let's create a function to build a TensorBoard callback. And so if we want to track our experiments, we might want to know, hey, when did we run this model? And what was the experiment name? So how about we set up a function that creates a folder based on a certain name of an experiment, because we could call it model 4, the experiment. That would be simple. Model 4, and then that way we want one folder that stores all of our training. And then we would have a folder with model 1, 2, 3, 4, and here's all the results stored in a folder. And then we could use that folder. Yeah, that's a great idea. Let's do that. All right. So I said a lot of stuff there, but it's probably going straight over your head if you've never heard it, but it's going to make sense once we code it. So create TensorBoard callback. And now we want to functionized because we need to create a new one for each model. We'll see what this looks like in practice. So we're going to start by importing datetime, because we're going to use a date stamp, a timestamp for when our model was run. This will be helpful so we can know, hey, this model was run on last Wednesday, but the model on Thursday beat it. So what was the difference between the Thursday and the Wednesday model? And then we go def create TensorBoard callback, and we need a directory name. The directory name parameter is what we're going to use to create a file to store our TensorBoard callback. In other words, where our model training results are going to go. And then we are going to create an experiment name. So the experiment name is, say we want model 3 is our experiment, we could set it as the experiment name. So we'll set up a variable called log_dir, where the logs are going to go. And then it's going to be a combination of directory name, plus we need a slash here to create a file path. And then we're going to go plus experiment name. And then we'll go plus, we'll add another slash here. And then we're going to get the current timestamp. So whenever this is created, datetime.now.string from time. And then we're going to set it as, we'll go year first, then we'll go month, then we'll go day. You can get specific as you like here. And then we'll set it up as hour, minute, seconds. Okay? Fair bit going on here, but what this is creating a directory path of where to store. So the directory path is going to be the directory name slash the experiment name. So there's a subdirectory with the experiment name slash the date time. So that's when we ran our specific experiment. And then we go TensorBoard. We'll create TensorBoard callback equals tf.keras.callbacks.TensorBoard. And now where does that come from? It comes from the callbacks module. So if we click on TensorBoard, tf.keras.callbacks.TensorBoard. Now you see how the first parameter is log_dir. We go down, what does log_dir say? The path of the directory where to save log files to be passed by TensorBoard. So if we come back in here, well, we've just created log_dir. So let's set that up. We'll go log_dir equals log_dir. Wonderful. And then we'll print out just a little notification here to tell us saving TensorBoard log files to log_dir. Wonderful. And then we will return the TensorBoard callback. Alrighty. So we went through a whole bunch of steps just then. Let's go back through what we've said. So we're setting up callbacks. This is a very important concept in model training as you start to build larger and larger models and run lots of more modeling experiments. They become even more important. So tracking experiments, we can track them with TensorBoard. We'll see exactly what TensorBoard is shortly. Model checkpointing. If we're training our model we've only trained models for really 5 epochs, but let's say we train them for 1,000 epochs or just indefinitely, and we wanted to checkpoint it, say, every 10 epochs, so that if training fails or something, at least we've got a checkpoint saved somewhere. And then early stopping is another very popular callback, which is we could set our model training as long as it likes, but as soon as it stops improving some metric, such as validation accuracy, it stops. Now, we've only spoken about these two in words so far. We'll see them in action later on. And so, now that we've got a callback ready to go, how about we start preparing to build our first transfer learning model? We'll see this in action once our model is ready to train. Now we're up to a very, very exciting point. I'm going to introduce you to one of my favorite TensorFlow resources, and that is TensorFlow Hub. We're going to write a heading here, creating models using TensorFlow Hub. All right. Now, let's just have a look. All right. So to get to TensorFlow Hub, we can search TensorFlow Hub, and we could go to TensorFlow Hub on the TensorFlow.org page. Let's see what it says. TensorFlow Hub is a repository of trained machine learning models. Oh, that is beautiful. And look at this. Look how quickly we can start to use a TensorFlow Hub model. We've got import TensorFlow Hub as hub. We haven't seen that before, but we're going to practice. We set up our model in one line of code. And then embeddings, we pass. This is a natural language processing model here. We pass it to our model. Wow, this is absolutely amazing. So models. So find train models from the TensorFlow community on tf.Hub.dev. Let's go there. I'm going to grab this. We'll copy that. And we'll go here. We'll write down what we've been doing. So in the past, we've used TensorFlow to create our own models layer by layer from scratch. Right? So now we're going to do a similar process, except the majority of our models layers are going to come from TensorFlow Hub. We can access pre-trained models on tf.Hub.dev. Now, let's explore. What are we looking for? What are we working on? We're working on food vision. So image classification. So let's keep that in mind when we're exploring TensorFlow Hub. Okay, tf.Hub.dev. I'm going to explore. There's a lot going on here, just like the TensorFlow documentation. Welcome to TensorFlow Hub. TensorFlow Hub lets you search and discover hundreds of trained, ready to deploy machine learning models in one place. Oh my goodness, look at this. We've got problem domains, image, text, audio, video, depending on what problem you're working on. What are we working on? We're working on images. Wonderful. Oh my goodness. Look how many problem domains that there are. What TensorFlow version do we want? Well, TF2, that's what we're working with. Okay, so we'll start to filter out. Let's explore this. Problem domain. We don't want image augmentation, image classification. Yes, that's what we do want. We want image classifier. That's a bit confusing, but let's get rid of that. Image feature vector. Oh, we do want that. Object detection? No. Remember, we're working on food vision. Pose detection, RNN agent, segmentation, style transfer, super resolution. No, thank you. Okay, so we've narrowed it down to a few things. What have we got here? What's feature vector? We've discussed that briefly. Okay, feature vectors of images. This is what I was talking about, of MobileNet v2 trained on ImageNet. We haven't even seen what ImageNet is. ImageNet. Here we go. ImageNet is an image database organized according to the WordNet hierarchy. We're not going to go through that. What you need to know about ImageNet is it's a very big database of images of whole different classes. So what we'll notice is a lot of these models here, the feature vector ones, are trained on ImageNet. So we could keep scrolling through here for as long as we want. There's a lot of models here, almost too many. So to kind of fix things up, how about we narrow this down? So I might go into architecture, and I just want efficient net B0, and what else do I want? I also want maybe ResNet V2 50. Okay. Now, you might be thinking, Daniel, where did you even get the name EfficientNet from? Where did you get the name ResNet from? I've never even heard of these things. Well, this has only come from experience with working with deep learning models. And you're going to come across a heap of models in your work with deep learning that are named quite strangely when you first begin. Now, the reason why I chose these is typically when you're working on some sort of problem and you want to use transfer learning with your problem, you want to use the model which has worked best in your particular problem domain. And so how would we find a model that is working best in our particular problem domain? So ResNet, I'll just let you in a little secret. ResNet is a very good image classification model, same with EfficientNet. But if we wanted to find which model is performing the best, we can go to a website called Papers with Code. This collects all of the latest research papers in deep learning and puts them into one place. Browse state of the art. Here we go. Now, again, there's going to be a lot of stuff here that you're not quite sure of, but I just want you to start to get familiar with these resources because you're going to come across them later on in your deep learning journey. So what are we working on? Computer vision, image classification. Okay. So this is where researchers from top universities and top companies publish their paper. So a research paper. You can often find code as well. And this is going to tell you which architecture is performing best on image classification. So image classification is a fundamental task that attempts to comprehend an entire image as a whole. So here we go. So this is the best method so far on ImageNet. So EfficientNet L2, meta pseudo labels, that's from the paper. So again, a lot of information here. I myself even look at these things and I don't understand what's going on. So I just want you to get familiar with this kind of resource. Just to let you know, not always the model which is performing best is the best for your problem. Because a lot of these models take a lot of different techniques and whatnot. They're not as straightforward as what we've been using. So that's just something to keep in mind. But that gives us the name EfficientNet, which is when we come back to TensorFlow Hub, we found EfficientNet. So of course you could dive in and read the EfficientNet paper if you wanted to. EfficientNet paper. Rethinking model scaling for convolutional neural networks, and that'll tell you all about EfficientNet. But the beautiful thing is that oftentimes when a new model has come out and it's performing really well on a certain type of problem and lots of people are getting use out of it, it goes up to TensorFlow Hub so that we can access it. So that was a lot of talking and I showed a lot of resources. We haven't done quite much coding, but let's see how we might use the EfficientNet B0 feature vector one model. So we've got EfficientNet B0 classification, but we want feature vector, and this will be clear why shortly. So we click into here, image feature vector, feature vectors of EfficientNet, models trained on ImageNet, wonderful. So we can download that. Model formats, tf2 saved model. Oh, we've seen the save model format. Now, requires TensorFlow 2.2 plus. Okay, we can download that if we wanted to, or we can copy this URL. What does this look like if we just copy that? So there's the paper it came from. Training. Usage. This is how we use it. Wow, okay. We can put it into a model, tf sequential, hub. All right. Number of classes. Okay. Let's give this a go. So we'll come back to our notebook and we'll put in here, browsing the TensorFlow hub page and sorting for image classification, we found the following feature vector model link. All right, so there's our EfficientNet B0 feature vector. So before we put all the pieces of the puzzle together, so in the next video, we're going to start to see how we can use this link into building a model. I'd like you to spend 10 minutes exploring TensorFlow Hub just off a whim. And then if you see something like this, ResNet v250, I want you to Google that. Just Google what ResNet v250 and what does that mean? Even Google EfficientNet b0 and see what that is. Why is there different numbers of EfficientNet? So just give that a go. I'll give you a little hint, is that oftentimes in deep learning, the higher the number, the more complex the model. So that's just one tip. But give that a go. Spend 10 minutes just exploring TensorFlow Hub, and in the next video, we'll start to put together the pieces of the puzzle, and we'll see how we can create a feature vector. Remember, in part 1, feature extraction. We'll see where feature vector comes into play. We'll see how we can create a feature extraction model using our pre-trained EfficientNet feature vector model. Whoa, we said feature a lot there, but again, it'll be a lot clearer once we write the code. So browse TensorFlow Hub, see what you can find, and I'll see you in the next video. How'd you go? Did you explore TensorFlow Hub? You know what? In the time between the previous video to now, I've had an idea of what we can do to really, really practice what we've been talking about. Callbacks, feature extraction, the whole lot, transfer learning. What we're going to do is pit two models against each other, two TensorFlow Hub models. So this is ResNet v250. So again, you might not have ever heard of this, but what you should know is ResNet, it should come up, ResNet Deep Residual Learning for Image Recognition. So this is another paper. When this model got first introduced, this is where ResNet comes from, so Residual Neural Network. It did incredibly well on the ImageNet test. There we go. This result won first place on 2015 classification. So this is where the ResNet model came from. We don't have to replicate it. We can use it from TensorFlow Hub. And let's see, to get practice using TensorFlow Hub, we're going to, let's compare the following two models. We'll go ResNet URL equals that model there. And then we've already got our EfficientNet B0, EfficientNet URL. Did I spell EfficientNet right? Efficient URL. I am prone to typos. Okay, so we've got two URLs. This is beautiful from TensorFlow Hub. Now we'll go here. We could start importing some requirements, but I just want to show you this slide to really drive home the power of TensorFlow Hub. What is TensorFlow Hub? We've kind of discussed it already. A place to find a plethora of pre-trained machine learning models ready to be applied and fine-tuned for your own problems. So what are we working on? We're working on food vision image classification. So maybe we find a model that's pre-trained on ImageNet. What could that be? So maybe we find this on TensorFlow Hub. This is the URL that we can use. So TensorFlow makes using a pre-trained model as simple as calling a URL. So what you should be asking yourself when you're working on any kind of deep learning problem and you want to use some sort of existing architecture, does my problem exist on TensorFlow Hub? And that's where you can come in here, TensorFlow Hub, go to here, problem domains. Are you working with images? Are you working with text? Are you working with video? Are you working with audio? And then start to go through here. But now, enough talking, Daniel. Let's get hands-on and build our first model using TensorFlow Hub. So we're going to need a few dependencies. Import dependencies. And we'll go import TensorFlow as TF. Import TensorFlow Hub as Hub. You're going to notice we've built some models from scratch in the past few, well, we've built a lot of models so far, but now you're going to see, I'm actually so excited. I can't hide it. I feel myself smiling so much because we're going to see how incredibly powerful transfer learning is, building a model with a single URL. So in the past, we've written a whole bunch of model code to create models. We've built them from scratch each time, but let's start to functionize it. So let's make a create model function to create a model from a URL. Ready? This is going to be absolutely wild. Def create model. What do we need? We need a model URL, and then we need num classes. How many classes are we working with? We're working with 10. That was a spoiler alert. Train 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We already know this. So we've got 10 food classes. And again, this parameter could be changed depending on what we're doing. So we'll put a doc string here. So takes a TensorFlow hub URL and creates Keras sequential model with it. Oh, we're getting that warning again. We're going to use the GPU shortly, Colab. Bear with us. Args equals, we want model URL. We're writing some very Pythonic code here. A TensorFlow hub feature extraction URL. We haven't quite covered what feature extraction or feature vector means just yet, but we will. Or we have glazed over it in a previous video, but we're going to see it in the context of transfer learning in a second. So the number of classes is number of output neurons in the output layer. So should be equal to number of target classes, default 10. Maybe we'll tab that across so we know. And then what does it return? Returns an uncompiled Keras sequential model with model URL as feature extractor layer and dense output layer with num classes output neurons. Woohoo! Now that is a beautiful looking doc string. Ideally, any function that you write, you'll have some sort of doc string like this. This is in the Google Python docstring format. So you can look that up, and that's just the style that they like to write their docstrings in. So now, here we're going to write our model creation code. So we're going to download the pre-trained model and save it as a Keras layer. Now, I'm not just pulling this from anywhere. So if you go into TensorFlow Hub, all of the models have example usage. So see here, tf.Keras sequential, we're about to write this. hub.keraslayer.url trainable equals false. We haven't covered that yet, but we will, one step at a time. Let's write the code first. I'm going to stop jumping around and we're going to finish writing this code. So the feature extractor layer equals hub.keraslayer, and we're going to pass it in the model URL. So wrap to save model as a Keras layer. So what do you think that's going to do? So as a Keras layer, that just means that we're going to be able to put this entire model into a Keras sequential model, just like we've been putting layers into our Keras sequential models in previous videos. And we're going to set trainable equals false. Now, you might be wondering, why are we setting trainable equals false? It's like, aren't we going to train this model? And yes, we are, but I'll give a little hint as to what we're going to do. Freeze the already learned patterns. So remember, these models have been pre-trained on ImageNet, so they've learned patterns in ImageNet. So we want to utilize those patterns from ImageNet for our food vision problem. Actually, let's give this a name so we know what it is. Name equals, we'll be creative, feature extraction layer. And then we'll define the input shape as image shape plus 3. Now that line that we just did is a fanciful way of creating our image shape is up here. All right, so we just did a fancy way of turning it into the image shape that we've been using before. So if we do image shape plus 3, I keep typing it in the short version, image shape plus 3. It just turns it into that. All right, so that's just a syntax hack for doing that. Okay, now let's create our sequential model. Create our own model. We're going to do model equals tf.Keras.sequential. We've seen this before. Now we want to actually start off with the feature extraction layer. Feature extraction layer. So, layer would help if I type that right. So what this means is, because it's sequential, means our input image is going to go through this model first. And then we're putting our own layers.dense. we're putting our own dense layer on the top. So activation, what's the activation for a multi-class classification problem? Softmax. And then the name can be output layer. All right. And then we need to return model. Far out. We covered a fair few steps there. So we're going to compare the following two models in our own dataset. Let's start with the ResNet URL. So let's create a ResNet model using our function. We'll test out our create model function. So we'll go create ResNet model. Actually, we'll put in here creating ResNet TensorFlow Hub feature extraction model, just to break up our notebook, creating and testing. Wonderful. Create ResNet model. So we can go ResNet model equals our create model function. What does it take? Look at that. See that? That's our own doc strings from the function that we just wrote. It takes a TensorFlow Hub URL and creates a Keras sequential model with it. Look at that. That's how beautiful. This is Colab in action. Because we wrote that doc string, this is what pops up for us. We're helping our future selves with the code that we've been writing. Or if someone else came across our code and wanted to use it, they might not be too horrified because we've actually got some doc strings. So num classes equals train data 10% num classes. There's another attribute you can use, num classes. We could always just leave it as the default 10, but just for completeness, I'll just show you what this looks like. Wonderful. And so ResNet URL, I've got a typo here, of course, is not defined. ResNet model. Now what's the key point here? It returns it uncompiled. So what do we have to do? We have to compile our model. Oh, what have we got? Keyword argument not understood, trainable. Another typo. Trainable equals false. Let's run this. Feature extraction layer is not defined. Look at all these typos we've got. Feature extractor layer. What do we want to call it? Extractor or extraction? Extractor. And what other typo are we going to come across? None. Okay, beautiful. Can we get a summary of that, or do we need to compile it? ResNet model dot summary. Whoa, that is a lot of total parameters, but do you see what happened here? We have non-trainable parameters. We haven't seen non-trainable parameters. That's always been 0 so far. The only trainable parameters is the output layer. So that's the only patterns that are going to train, is our output layer. Because we've set trainable equal to false, our feature extractor layer is not trainable during training. So we'll see what that looks like visually in a second. But let's compile. What do we do after we create a model? We compile a model. Compile our ResNet model. So ResNet model dot compile. What's our loss function going to be? We're on a multi-class classification problem. Let's use categorical cross entropy. What's our optimizer? Our friendly atom, tf.Keras optimizers.atom, and our metrics can be accuracy, just like the computer vision models we've been building in the previous module. Let's compile, and we're actually ready to train this model. So this is very exciting. Are you ready to destroy all of the results that we've got building our own models? Because I hope you are. So I'm going to issue you the challenge, because we've just compiled this. Before we go ahead and train this, I'd like to issue you the challenge before the next video is to fit this on the training data, just like we have all of our other models, and see how it goes. Train it for 5 epochs. If you really want to challenge yourself, pass the callback, the TensorBoard callback that we created before to the fit method, and just have a look at the results. I just want you to see what the results are, and remind yourself that this is training on 10% of the data. So once it finishes fitting, if you go through the challenge, go back to our O3 notebook, find the best results in here, and see what happens. All right, so there's your challenge. But I'll see you in the next video. Get excited, we're about to fit our first transfer learning model. Can you hear that? That's me rubbing my hands together because I'm so excited. We're going to blow our previous models out of the water, and all without even putting together our own layers. This is all we've done. Look at our model. Our model is like 4 lines of code. You ready? Let's fit it to the data. So we're going to can that and go, let's fit our ResNet model to the data. 10% of 10 classes. Just another reminder, we're only using 10% of the training data here. So we'll save it to ResNet history, just so we know. I'm going to go ResNet model dot fit. We can pass in train. Actually, you might have already given this a go yourself. That was my challenge for the last video. How'd you go? If so, did you see the results? I don't want to give any spoiler alerts, but woohoo! Equals len train data 10%, and then we want to pass in the validation data. Remember, the validation data is the exact same that we used in our previous notebook. Hasn't changed. It's still the test data, 10 classes, 250 images each. And now we're going to see, this was the extra challenge. You see in the fit function, it has a parameter for callbacks. Previously, we haven't really used that, but now we're going to do so. So let's pass in our callbacks. Callbacks has to be in the form of a list, and our callback is a function, create TensorBoard callback, which requires a parameter dir name equals, what should we call it? TensorFlow hub. We'll save our models into that directory, and we'll also pass it experiment name. And this is going to be ResNet 50 V2. And if you're wondering where ResNet 50 V2 came from, that is from the model URL, ResNet V250. Oh, we could have really done that the other way around, doesn't really matter. ResNet 50 V2. Okay, are you ready? This is our first transfer learning feature extraction model. If there's no typos, this code should run and it's going to be very, very exciting. So let's do it. Of course there was. Validation data. And then we can also do validation steps, can't we? Did you pick up on that? Did you pick up that I missed that? Don't necessarily need it, but we'll put it there anyway for completeness. And you ready? 3, 2, 1. First transfer learning model going off. Look at that. This is our saving TensorBoard log files. This is our little helper function to TensorFlow hub /ResNet 50 V2. And that's the current timestamp. And so if we go into here, we've got TensorFlow hub, and then inside that is ResNet 50 V2. We're going to see what this is later on. But look how quick that is. Look at that. Oh my gosh. So while this is fitting, let's discuss what's actually going on. We've only got about 20 seconds per epoch, so we better be quick. This is what we've built, a ResNet 50 * feature extractor. So our input data is 10 classes of food 101, 75 images of each class. We've got sushi, steak, ice cream, oh, delicious ice cream, pizza, hamburger. We pass it through this model. Now, this is a massive architecture, ResNet 34. In the code, we're using ResNet 50, a slightly larger architecture than ResNet 34. If you counted up those, I think there's 34 there. So ResNet 50, as you imagine, is bigger. If you look closely, this is a 3x3 convolution, 3x3 convolution, 3x3 convolution. But the key point of ResNet is that it has these skip connections. We're not going to dive too deep into that. There's a lot of blog posts online covering that if you want to dive into the specifics. We're just trying to apply it to our own problem. You can find out, this is from the ResNet paper. So all of these layers, all of the patterns that they've learned, they stay the same, right? Because we put trainable equals false. So they're frozen. These layers, all their patterns are pre-trained on ImageNet. What we're changing, if you see here, the original ResNet layer had an output layer for 1,000 classes. So that was for ImageNet. But how many classes do we have? Remember, deep learning is all about input and output shapes. We have 10 classes. So what do? We change the output layer. Instead of being an ImageNet 1,000 classes, we change it to 10. So this changes to be the same shape as the number of classes we're working with. So this is what we've built, a ResNet 50 feature extractor. A feature extractor, the majority of the underlying layers stay the same, so our images go through here. It outputs a vector here of whatever the patterns have found in that image, and then our layer here, this dense layer, converts that feature vector into a tensor that's related to our 10 classes. So let's go back and see how our model's gone. It should be finished training now. How quick was that? Now, oh my goodness, look at that. 90% training accuracy on 10 classes, only 10% of the data. And validation accuracy, we're pushing close to 80. Let's just go back and remind ourselves of what we got in our previous notebook. So this is, again, we have to come to multi-class classification for image classification. We built Model 10. Where is it? Model 10. Model 10. Do we have a summary of Model 10 anywhere? Model 10 is the same as Model 8. So we got convolution, activation, convolution, max pooling, convolution, convolution, max pooling. The same as what's on the CNN Explainer website. And if we come down here, how long did that take? We had to use data augmentation and a whole bunch of different things. It took 100 seconds per layer. And what did we end up with? Validation accuracy of 40, not even 40%. And we've just used ResNet 50 V2. It's trained in 1/8 of the time, but we've got basically double the results on the validation data set. What did I tell you about transfer learning? That is the power of transfer learning. So what do we have to do? We have to plot the loss curves. So let's write our, or can we even just copy our loss curves function from the previous notebook? No, we'll write it out. So transfer learning, let's just write ourselves a note here. Wow. That is incredible. Our transfer learning feature extractor. So remember, if we come back to our keynote, all of these layers, so this is the ResNet model that we imported from TensorFlow Hub, all of them have been pre-trained on ImageNet. So they already have some patterns of what images look like. All we did was like, hey, ResNet model, look at our images. What do you think? Put out some patterns that you find, and then we've trained the dense layer on the end here to conform to our own custom classes. So that's feature extraction transfer learning. We'll come back. Our transfer learning feature extractor model outperformed all of the previous models we built by hand substantially, and in a quicker training time. So that is the incredible power of transfer learning. We can get incredible results. I forgot. And with only 10% of the training examples. We didn't even use the full data set. We've got another, however many images, we've got another about 700 images of each training class if we wanted to step up our results. So what's a good thing to do is to plot loss curves. So let's create our function here. So let's create a function to plot our loss curves. So we've saved our ResNet model's training history to ResNet history. We've also saved it here to TensorFlow Hub. So I'd like you as a challenge to create a function to plot our loss curves. If you want some reference, we've got a function in our previous notebook, O3. You might need to replicate this function. And then we'll see what our loss curves look like for our ResNet feature extraction model. So that's your challenge. I hope you're amazed as I am at the power of transfer learning. Transfer learning still blows my mind. But yeah, give a shot at creating a plot loss curves function. If you really want to, test out plotting the loss curves of our ResNet model. I'll see you in the next video. Oh, I'm still buzzing from the amazing results we got from our transfer learning feature extraction model. We need to evaluate our model. So it's one thing to train a model. The next most important thing is to evaluate it. So let's create a function to plot our model's loss curves. Now, We did make this in O3, so the challenge was, did you try creating the function yourself? If not, that's completely fine. Let's see how we can do it together. I mean, just a tidbit. You could put a function like this into a script called something like helper.py and import it when you need it. So you could, if you find yourself using functions over and over again, like we do when we're doing a lot of experiments, you might want to create a helper script like helper.py, upload it to GitHub, and then every time you start a notebook, you could go from helper, import, plot, loss, curves, something like that. So that's just a tidbit for going forward. That's a little like software engineering thing. But because we're machine learning practitioners, we write all of our code in notebooks. And pyplot, we need matplotlib because we're going to be plotting. And then we want to plot the validation and training curves. We go def plot loss curves, history. And we could put in a little docstring here. Returns separate loss curves for training and validation metrics. And we go args history is a TensorFlow history object. And then returns, and we want plots of training / validation loss and accuracy metrics. Now, I just realized that's one part where this function will fail, is that if we're using a metric that's not accuracy. So if you created your model and compiled it with a different metric here, that's where this function would fail. So that's just something to know going forward, is that depending on what metric you're using, so far we've only been using accuracy, history, and then we want loss, and then we want, what else do we want? We want val loss equals history dot history, val loss, and we want accuracy. Oh, this is going to be so cool. So cool to see the training curves of our first transfer learning model. It's already blown all of our previous models out of the water. All of those models we spent crafting hand by hand, writing the convolutional layers. I mean, TensorFlow did take care of a lot. This is just the loss. And this is the accuracy of our model training. TensorFlow did take care of a lot of things behind the scenes for us when we wrote those layers. But if you can use transfer learning and get better results with less data, because here's an important point. We downloaded, now I'm going to plot the loss. We downloaded a pre-made data set. But on your own projects, you're not always going to have a pre-made data set. So if you can collect less data for whatever you want to work on, if you're working on an actual food vision application, you might not have access to 750 images of whatever you're working with. So you might only have 20. And so if transfer learning performs really good with less data because it's using the patterns that it's pre-learned on other problems, well then, that's a good thing. Now we need xlabel, plt.xlabel. I was kind of just talking out loud there while I was coding. Now we need a legend. And what else do we need to do? Plot accuracy. You see how importing this from like a helper.py would be really good? Maybe we'll do that in a future module if we're typing out too many functions. We'll see how we can create a helper script for ourselves. Plot.figure, plt.plot, because what's the coder's motto? Don't repeat yourself. Machine learning practitioner's motto, experiment, experiment, experiment. And now we're doing some data visualization or data exploring motto here. This is visualize, visualize, visualize. Plot epochs, val accuracy, label equals, val accuracy. Wonderful. plt.title, accuracy, and then plt.xlabel, epochs, and then the final one is plt.legend. This should work, hopefully. That took a little while. Run, and now plot loss curves, resnet history. Boom. Oh, would you look at that? Oh, so what were we trying to fix in our previous module? We were trying to get these curves as close as possible. And this is pretty close, although the validation loss seems to be not going down as fast as the training loss here, so hinting that our model might be overfitting. Remember, if validation loss is increasing while training loss is decreasing, that should trigger a light bulb in your head and go, my model might be overfitting. In other words, learning the training data too well. But this is good here as well. They're fairly close, whereas compare that to a loss curve in our previous one. Validation loss is all over the place. It was a little bit better there because we did some tricks like data augmentation, but way better than that. Look at that. That's just complete mud, isn't it? Far out. Okay, so our model is going good. That's our first transfer learning model. So exciting. What were we doing? We set up an experiment. We've done creating and testing ResNet TensorFlow Hub feature extraction model. What did we say we wanted to do? We want to compare ResNet to EfficientNet, specifically ResNet V250 to EfficientNet B0. So let's do that. I'm going to copy this heading. We'll do that in the next video. So creating and testing, we'll come down to where we were. Text, creating and testing EfficientNet B0 Tensor Hub feature extraction model. So your homework before the next lesson is to think about, or you could even try do this yourself. What would we have to change to use EfficientNet B0 instead of ResNet? So that's your challenge. And then you can also look up, if this is what ResNet feature extraction looks like, try and find a picture that's similar for EfficientNet. So you could Google EfficientNet B0 architecture and then see how that relates to something that looks like this. So you might not understand what's going on in every single layer, but that's okay. But these are the kind of diagrams you're going to see when you get involved in deep learning. These are just layers connected. We've built models like this. This is just a bigger version. So that's your challenge. Try and do that. In the next video, we'll build an EfficientNet TensorFlow Hub feature extraction model, and we're going to see how that goes against ResNet. And I think EfficientNet is going to blow our previous models, so in the O3, out of the water as well. But the big battle right now is ResNet versus EfficientNet. So give that a try, and I'll see you soon. All right, we saw how well ResNet 50 or V2 did on our dataset. Now are you ready to blow our previous experiments results out of the water? So what are we trying to beat here? This is our previous notebook where we built Model 10, got a validation accuracy of 39%. And it took about 110 seconds per epoch to train because we did a bunch of data augmentation. And we saw ResNet 50 V2 gets even better than that. It gets 75% accuracy on the validation dataset using only 10% of the data. And it only takes 16 seconds or 27 seconds for the first epoch, but then it speeds up for the later epochs. So now let's see how EfficientNet goes. What we'll do, we'll create EfficientNet B0 feature extractor model. Before we write any code, I just want to remind you what we're creating. So this is a ResNet 50 feature extractor that we just created. And the note here is that this is actually just a 34-layer ResNet rather than a 50-layer ResNet. What we're going to do with EfficientNet is just a different name of a different kind of computer vision architecture. We'll have the same input data. We're going to have the same output layer, except we're going to change these layers in the middle here. Instead of using ResNet 50 V2, we're going to substitute in EfficientNet B0. And how do we do that? Well, we can do that with our TensorFlow hub URL. So let's write in here, EfficientNet model, and we're going to call it, we're going to use our function create model. We'll type in model URL, and then we can type in EfficientNet URL. Beautiful. And then the number of classes, we could leave that as default because here from our docstring it is 10, but we're going to set that to train data 10%.num classes, just so we're doing it nice and officially. Now we're going to compile our EfficientNet model. So we'll go EfficientNet model dot compile. And what are we using for the loss? Since we're doing multi-class classification, we're using categorical cross entropy. And then for the optimizer, we are going to use Atom, tf.Variable optimizer.Atom. This will be the exact same as compile method as we did for our ResNet model. Metrics equals accuracy. So we could actually put this compile into our create model function. So that way create model would return a compiled model. So that's a little extension you might want to try out. Now we can fit efficient net model to 10% of training data. Alrighty, so let's go efficient net. I always get this efficient net history because there's so many ENT, NET. That's what confuses me when I try to type efficient net. We want to fit efficient net model on train data 10%. We'll do the same number of epochs. So this is where I was talking about before. We could have set epochs as a global variable if we're running a bunch of experiments. So we could have set epochs equal to 5 and then type in epochs here. And then that way we wouldn't have to retype 5 every time. So that's just something to keep in mind. On the validation data, we are going to use test data, which is just the same test data we've been using for the last few models. We're going to go validation steps equals len test data. And have you caught me out? Have you caught me out with what we forgot here? We forgot steps per epoch equals len train data 10%. Wonderful, we'll add a comma there. And what have we been doing? Something that's new in this notebook. We've been adding callbacks. So callbacks equals our create. We made a handy function for this, create TensorBoard callback. The directory name is, of course, going to be TensorFlow hub, because that's our existing directory over here, TensorFlow hub, and we can see in there's our ResNet 50 v2 model. So all of its training history is going to be stored in there. And so we're just going to do the exact same, but we're going to type in experiment name equals efficient.net. Efficient.net B0. Actually, we'll type it in there. Wonderful. All right. So are you ready to go? We're about to fit a pre-trained efficient.net B0 model on 10% of the training data. So just a little reminder what we've created. Exact same setup here, except now we're using an efficient.net B0 feature extractor. You could substitute out this architecture in here for efficient.net B0. Let's see if we can... Actually, we'll run this. You ready? And while it's fitting, because it's going to take a few seconds per epoch, we're going to explore to see where we can find out some information about efficient.net. We'll run that. Make sure there's no errors. This is so exciting. Efficient.net's one of my favorite architectures in the deep learning world of recent times. Here we go. Saving TensorBoard log files to TensorFlow hub efficient.net B0, and there's a timestamp. Epoch 1 of 5. Beautiful. Oh, look how quick that is. That is absolutely amazing. We don't have much time here. I want to just search up efficient.net. So there's a great blog post here from Google when that first got released. Here we go. Efficient.net, improving accuracy and efficiency through AutoML and model scaling. Here we go. The architecture for our baseline network efficient.net B0 is simple and clean, making it easier to scale and generalize. Beautiful. So this is the efficient.net B0 architecture that we're using. We've got a convolutional layer, we've got an MB-conv1 layer. If you want to find out more details about this, I'd recommend you check out the blog post, and then there's a paper in here as well describing what efficient.net is. But if we come down here, this is our accuracy. So how different networks perform on ImageNet. And so here's B0. So this is the number of parameters, millions. We'll have a look at this in a moment. Efficient.net B0 uses the least number of parameters, but still gets great results. And so here's our ResNet 50, or is ResNet 50 v2 there? I don't think it's listed. But as you can see, there's different variants of efficient.net. So B0, B1, B2, B3, B4, B5, B6, B7, performing at various levels of accuracy. However, the number of parameters increases. So I'll let you dig into that. How about we just copy this link and we come back here. Details on efficient.net. Wonderful. All right, how'd we go? 15 seconds per epoch. Oh my goodness. Look at that. Validation accuracy is 86% on only 10% of the data, with a training accuracy of nearly 90. Oh my goodness. Look at this compared to our ResNet model. We come up here, 75%. So we've seen, and about the same time per epoch. So we've just seen, just by using EfficientNet, we've increased our validation accuracy from our ResNet 50 model by over 10%. And if we come back to our previous model we built by hand, we've over doubled it. Over doubled our validation accuracy, and in almost 1/10 of the time per epoch. So 109 seconds versus 15 seconds. That is absolutely wild. Let's plot the loss curves. So this is power of transfer learning, right? Taking what one model has learned in one domain and applying it to what we need for our specific problem. EfficientNet history. Let's have a look. Wow. What have we been discussing? The ideal scenario for these curves is for them to line up. And look how close that's getting. It looks like they could keep going. I mean, if you trained these models, they're heading in the same direction. They could keep going. The loss could keep going down. Accuracy looks like it might be tapering off a little bit. So maybe that's a little extension if you want to go through and train it for another 5 epochs. See how high you can push this validation accuracy to. That is so exciting. All right. So we've seen how powerful it is that we can use EfficientNet B0. Oh, and by the way, that's another tidbit. We've only used B0 here. There's still B1, B2, B3, B4, B5, B6, B7. And maybe they're on TensorFlow Hub, so maybe that's something else you could look into. But there's something we have to look at. So we've seen the power of transfer learning. We've seen the power of feature extraction. There's one more type of transfer learning we actually haven't discussed. And we're going to look into it further in the next module. But I think in the next video, we'll discuss some other kinds of transfer learning, and then we'll dig into our TensorFlow Hub directory and see how we can look at the results of our models on TensorBoard. Oh, this is so exciting. I'm so happy you're being introduced to the power of transfer learning. I'll see you in the next video. Welcome back. In the last video, we trained our best model yet. An EfficientNet B0 pre-trained on ImageNet, downloaded from TensorFlow Hub and adjusted to our dataset. It got the best results, and we only used 10% of our training images. So 75 images per class versus 750 images. There's one more thing that we kind of forgot to go through in the last video, but we will check that now. So if you wanted to go EfficientNet model.summary, we'll just check out the number of parameters here. So total parameters, 4,062,357. The trainable parameters are only the ones in the output layer. All of the feature extraction layer stays frozen. So if we go back to our keynote, all of the layers in here, all of the patterns in this pre-trained architecture stay the same. All we're doing is updating this output layer. And again, this is for ResNet 50. But the same thing goes with EfficientNet B0 if you just wanted to substitute it in here. So if we come back here, let's compare it to our ResNet model.summary. Wow. So this one has 23.5 million total parameters. The only trainable parameters are the ones in the output layer. But our EfficientNet outperforms our ResNet model even though it has over 5 times the number of parameters. I guess that's where the efficient comes in the EfficientNet name. I need a drum roll after that, like dum. So that's just something to look into if you want to keep going. Oh, and one more thing. Or actually, no. Daniel, stop getting distracted. We said we're going to look at the different types of transfer learning. This is going to be more of a theory-based lecture, but we're going to have a look at some slides in the keynote. But we've already built one of the types of transfer learning. So we'll write down here, I'm going to call this one as is transfer learning using an existing model with no changes whatsoever. And then we have, or this could be, is whatsoever one word? I don't even know. E.g., using ImageNet model on 1,000 ImageNet classes, none of your own. This is the one we've done. So feature extraction, transfer learning. So use the pre-learned patterns of an existing model. So this is the type that we've just gone through, feature extraction of an existing model, e.g. EfficientNet B0 trained on ImageNet, and adjust the output layer for your own problem, e.g. 1,000 classes from ImageNet to 10 classes of food. And we'll turn this into Markdown so it makes sense. And then the final one is fine-tuning. We haven't had a look at this. This is going to be the next section, fine-tuning transfer learning. So use the pre-learned patterns of an existing model and fine-tune many or all of the underlying layers, including new output layers. Okay, so again, this is just words based. So as is transfer learning, very similar to what we've done, except we wouldn't even change the final layer in as is transfer learning. So you just take a pre-trained neural network, say ImageNet model on 1,000 ImageNet classes, and run it on another 1,000 classes the same as ImageNet. Feature extraction is what we've done. So we've taken a pre-trained model slash, for example, EfficientNet B0, trained on ImageNet, and adjusted the output layer for our own problem. So ImageNet's 1,000 classes to our 10 classes of food, and then fine-tuning. I'm not going to dig too deep into this, but you can read that sentence there. Let's get visual, because text on a page, not that fun. Here we go. Original model versus feature extraction. So this is the original model. We have the large data set down here, this little symbol, for example, ImageNet. And we have the input layer, layer 2, ... layer 234, 235. These are actually arbitrary numbers. I've just put them quite high, because if we have a look at this working architecture, e.g. EfficientNet, let's have a look. How many layers does our EfficientNet B0 feature extractor have? So we can get this by going EfficientNet model.layers, and it'll show us our layers. So see here, the first one is a TensorFlow Hub Keras layer, and that's the one we downloaded from TensorFlow Hub, all pre-trained, and this is our output layer here. So if we want to get specifically 0, wonderful, TensorFlow Hub, and we can go .weights. Weights is another name for pattern, probably the more formal name. I use patterns and weights interchangeably. So if we have a look at the weights of layer 0, look at this. These are all different patterns of numbers our EfficientNet B0 architecture has learned on ImageNet. So if I look at these and I have no idea what's going on, but the neural network, these are the patterns that it's learned in previous images. Look how many there are. So if we have a look, there's one of these tensors for every layer. Right, so there's a weight matrix for every layer. We could keep going, but that's going to take far too long. So what we can do is go len weights. So this will give us an approximation of how many layers are in our EfficientNet B0 feature extractor. So if we come here, this is what we're talking about. The architecture for our baseline network EfficientNet B0 is simple and clean, making it easier to scale and generalize. So that's going to give us an idea of how many layers there are in our EfficientNet model. So if you compare that, let's say 309, that might not be the exact number, but just going to give us an approximation. That's why I've put something like this, 235. A lot of modern architectures, it's not that rare for them to have over 100 layers. So if we compare that to the model we constructed by hand in our previous notebook, let's just find an example. Look at what we did. So we created this model 9. It has 1, 2, 3, 4, 5, 6 layers. Quite a simple architecture. Imagine how much time it would have took us to try and design something like this. So that's the real power of transfer learning, is if we come back to where we were, come back to our keynote, we can take a working architecture and apply it to our own problem. So this is the original model versus what we've done for feature extraction. So as we've said, the base layers stay the same. They stay frozen. That's something that you'll hear very often when we talk about transfer learning, is that these layers stay frozen during training. The original model layers don't update during training. The only layers that update are these two output layers. So where did we actually did that by design? If we come up to our create model function. So you see here, when we download the pre-trained model and save it as a keras layer, we've set trainable equal to false. That is what creates this setup, that these layers stay frozen. And now for feature extraction transfer learning, we have a different data set. Another key point here, it's similar to ImageNet. It's still images. So we've got 10 classes of food from Food 101. And what have we changed here? Because remember, a very important point in deep learning is the input and output shapes of your model. So the output layer shape in this case was ImageNet, 1,000 classes, but ours, the output layer shape matches the number of input classes that we have. And so this is what changes between an original model and feature extraction transfer learning. And the output layer gets trained on new data. All of this stays the same. A feature vector comes out here, goes through our final dense layer, and then our softmax activation, in the case of multiclass classification, outputs a prediction probability for what class it should be, based on the inputs. So there's a lot going on here, but we've written the code to do this already. So that's how I like to do things. I like to write the code first, and then when you look at the theory, you're like, wow, I've actually already done this. So I'm starting to putting the pieces of the puzzle together. But as we discussed, there's one more type. We put down 3 dot points here. So let's compare all of them. This module is all about feature extraction. We're going to have a look at fine-tuning later. But let's just introduce it while we're on the topic of kinds of transfer learning. So here's the original model. We just saw that. For feature extraction, the data set changes. However, the layers stay the same. They stay frozen. And the output layer changes. And then if we go to fine-tuning, the output layer stays the same. However, in fine-tuning, we might unfreeze some or all of the layers in the underlying model. And the data set might change. So that's the major difference between fine-tuning and feature extraction, is that in feature extraction, all of the layers generally stay frozen except for the output layer, whereas in fine-tuning, we might unfreeze some of the underlying layers and update their parameters or weights with our own custom data set. However, as with feature extraction, these layers start off with the patterns they've learned in ImageNet. And just a little tidbit for fine-tuning, it typically requires more data than feature extraction. So we're going to have a look at that in an upcoming module. However, just keep this picture in mind for the different kinds of transfer learning you're going to come across. That's about all we're going to say for now on the different types of transfer learning. Let's write some more code. In the next video, we're going to comparing our model's results using TensorBoard. Alrighty. So we're going here, TensorFlow Hub. This has got all our model training results. We're going to see conclusively which model performs better. So I'll see you in the next video. We'll find out what TensorBoard is, and we'll see how we can use it to track our experiments. We've already got some phenomenal results by using the power of transfer learning and feature extraction. And we've actually compared our models already. Like, we've got validation accuracy here. Why don't we just look at that? Why don't we just keep doing that? Well, you might have guessed this is going to become problematic if we were to run more than 2 models. What if we had a dozen models and we just had to keep scrolling back up and trying to keep track of which one was the best? That's not a very fun time. But thanks to our create TensorBoard callback, our model's training logs have automatically been tracked in this little directory here, TensorFlow Hub. So let's start to explore what is TensorBoard. So we'll go into the keynote. TensorBoard is a way to visually explore your machine learning model's performance and internals. And you can even host, track, and share your machine learning experiments on tensorboard.dev. TensorBoard also integrates with websites like Weights and Biases. Weights and Biases make some of my favorite machine learning tools, so that's a big shout out to them. Go have a look at their website. We're not going to go through that in this course, but the things we do with TensorBoard can link into Weights and Biases. And this is what we're going to end up with, something like this. And so see here, this is a few comparisons of our different model names and experiments. But rather than just look at the slide, let's start to code this up. And we can also find information on TensorBoard by going, what is TensorBoard? TensorBoard. TensorBoard. Here we go. A whole bunch of dot points which echo a little bit more information than what we described in the slides. And we've even got tensorboard.dev, which lets you easily host, track, and share your experiment results. Let's click on that. Beautiful. Let's see how we can start to use this and get something like this to track our modeling experiments. There's a little tidbit here. If we do use tensorboard.dev, this is a warning. So I'll say this before we start tracking anything. Note, when you upload things to tensorboard.dev, your experiments are public. So if you're running private experiments, things you don't want others to see, do not upload them to tensorboard.dev. So that's very important. So the experiments that we're about to upload, so the training results from our different models, they're going to be publicly available. Something to consider in all of your machine learning projects. If you are publishing things, make sure what you're publishing is allowed to be public, because if it has to be private, well then you can run into some problems later on. So we can use the TensorBoard command in Colab, which is pre-installed. So upload, if you're not running this in Colab, you'll have to go through the tensorboard.dev documentation to see how you can do this from your local machine. It's actually not that hard. There we go. Pip install u TensorBoard. However, TensorBoard comes pre-installed in Colab. So if you are running this in Colab, I'm running this in Colab, it should work straight out of the box. So upload TensorBoard dev records. Where are these coming from? We're reminding, we've got in here our TensorBoard logs. If we keep going into this directory, train, and we have a bunch of results, events.out, tf events. We're not going to go through all those. All you need to know is they contain our training logs of our 2 experiments, thanks to our create TensorBoard callback function. So we can upload our records to TensorBoard by going TensorBoard dev upload, and then we have to pass it a few flags. So one is log_dir for log directory. So where are the files stored? Ours are stored in TensorFlow hub, which is just the directory name here. This will be different depending on what you call your different directories for tracking experiments. So we can do there, log_dir, and then we're going to pass it the name flag. So this is going to be the name of the experiment that we upload to tensorboard.dev. So efficientnet B0, this is our experiment, versus resnet 50 V2. So of course, you can change that to whatever experiment you're running. Then we're going to pass it a description. And we're going to call it comparing 2 different TF hub feature extraction model architectures using 10% of the training data. You can get as creative or as non-creative as you want with a description. And then finally, we're going to write one shot here, which is once the files have finished uploading, one shot is going to exit the uploader. So let's see what happens when we run this command. If everything works, we should get a TensorBoard experiment ID. So TensorBoard uploader, This will upload your TensorBoard logs to tensorboard.dev from the following directory. Beautiful. Here we go. Here's our warning again. This TensorBoard will be visible to everyone. Do not upload sensitive data. And then this notice will not be shown again while you are logged into the uploader. To log out, run TensorBoard dev auth revoke. Continue, and we're going to type in yes. So to authorize this, I'm going to click on this. This is going to bring me to a page where I need to sign into my Google account, and then it's going to give me a code. So I'm going to go through this step. I'm going to get the code. However, I'm going to blank out my code. You should do the same too. Don't show anyone your secret codes. So once I click my account here, it's going to show me a secret code to allow me to use tensorboard.dev with my account. And if you share that code with someone else, they could potentially have access to your account. So that's the only step you're not going to see here. I'm going to blank this out. I just copied my code. I'm going to come back and enter my authorization code. Again, it's blanked out for a reason, so that if someone sees your code, they might have access to your account. Keep your codes private. I've entered the authorization code, and my experiments have been uploaded. Beautiful. Now we get a public link. I'm going to copy this link and write it here. Our TensorBoard experiments are uploaded publicly here. I'm going to turn this into Markdown. Beautiful. And I'm going to hide the output of this cell because it's got the code in it. Wonderful. Once you run that, authorize your account, enter your secret code. It's going to upload everything that's in the log directory to this experiment URL here. So we can view this. You ready? This is so exciting. Oh, look at what we've got. So this is our experiment name up here. I'm going to zoom in a little bit. Yeah, there we go. EfficientNet B0 versus ResNet 50 V2. Comparing two different TensorFlow Hub feature extraction and model architectures using 10% of the data. So if we come over to here, there's a lot going on. We're not going to go through every single thing because that would take too long. The TensorBoard documentation lists a whole bunch of stuff here. What we're worried about is the information. So we can see our EfficientNet B0, and there's the timestamp. Here's its performance on the training data. So if we toggle that, if we watch this, the orange line goes away. Wonderful. The same thing with the validation. That's our EfficientNet B0's performance on the validation. And then we've got ResNet 50 V2 on train and validation. And so these experiments here reflect the file paths that we've got in here. EfficientNet B0, timestamp, and train validation. Again, these were created with the create TensorBoard callback function that we passed to our model when it was being fit. So have a look. You can imagine how helpful this would be if we've only got two modeling experiments here, so maybe we only care about what we've got on the validation data set. How did our models go? Okay, so we can see here, the ResNet 50 model starts at about 50% or 56%, then EfficientNet starts at 75%, and then it keeps going, and they stay about the same distance away from each other throughout all 5 epochs. That is absolutely amazing. Now, again, imagine if we had 20 different experiments going on here. We could have them all saved down here, and then we could filter them to which ones we want to go. And we could easily just find which one performs the best by going to this point on the graph here. So there's the accuracy. The same thing with the loss. We see that the EfficientNet B0 model finishes with a lower loss value. Remember, the loss value is how wrong your model is compared to ideal predictions that it should be making. So this is powerful stuff. So there's a lot more to explore, but if you want to see what experiments you have, check out what TensorBoard. So say you've uploaded a fair few different training results. Check out what TensorBoard experiments you have. Remember, this URL is public. So if you click on that, you're going to see the same results that I've got there. Do not upload private data to tensorboard.dev. So we can run TensorBoard dev list. This is going to tell us the experiments that we have. All right, so here's my EfficientNet versus ResNet 50 V2. We get a whole bunch of information on when it was. I've got another experiment here, fine-tuning EfficientNet B0 on all Food 101 data. That might be a spoiler as to what's to come. Transfer learning experiments. I've got a whole bunch of different stuff. Here's another one I performed earlier on EfficientNet B0 versus ResNet 50 V2. And if you wanted to delete an experiment, so let's say you uploaded some private data and you want to get rid of that as soon as possible, well, you can go TensorBoard dev delete, and then we're going to go experiment ID, and then we would copy this experiment ID in there. So I could copy this and I could paste it here. If I ran that command, it would delete this experiment. However, I'm not going to run that because I want to leave this here so that when you come and visit this notebook later on, if you want, you can just click on that and the link will work for you. So that's just how you delete an experiment. And then again, if you wanted to confirm, that was confirm the deletion by rechecking what experiments you have left. So TensorBoard dev list. So then when we go in here and see, hey, did this experiment ID get deleted? To make sure it was, we would go, okay, that experiment ID doesn't exist. Good, it's no longer on TensorBoard. So I think that is it for Section 4, Transfer Learning in TensorFlow Part 1 Feature Extraction. We've covered a fair bit of ground, and it's a relatively short section compared to what we've done before, but it doesn't take away from the importance of what we've just gone through. So we learned at the start the power of transfer learning. We downloaded a data set. Of course, it was 10% of the food classes, so only 75 images per training class versus 750 we used in the previous module. We went back through creating data loaders. We set up a callback. We learned what callbacks are and some of the most popular ones. We created a TensorBoard callback to track our model training results so we could later compare them using tensorboard.dev. Here's our experiments here. Remember, this is publicly available, so you can go and have a look at what's there. We created a ResNet TensorFlow Hub feature extraction model. We built an EfficientNet B0 TensorFlow Hub feature extraction model. And we saw that EfficientNet performed absolutely amazingly on our training data and in far less time than some of the models we've built in previous modules. We went through the different kinds of transfer learning. The feature extraction was the one we focused on here. In a future module, we're going to go through fine-tuning transfer learning. And finally, we finished off by comparing our model's results using TensorBoard, a very, very powerful tool. If you want to learn more about TensorBoard, you can go into the TensorBoard documentation on TensorFlow's website, because we've only looked at it for one use case, and it's got a whole bunch more. Oh, and just one more thing while we're here. Weights and biases integrates beautifully with TensorBoard. So developer tools for machine learning, we're not going to go through that, but if you want to integrate weights and biases with your TensorBoard logs and track your experiments, very important point of deep learning is to track your experiments. You can do that with what we've created here. Far out. So I've set up some exercises and extra curriculum, which you can get in the GitHub, github.com, Mr. D. Bourke /TensorFlow Deep Learning. So all of the exercises, so this will probably be a little bit different by the time you watch this, but this table is going to be your ground truth for all of the course materials. If you want the exercises for this section, you can click Go to Exercises, and so here we go. So here's the exercises and extra curriculum for this section. So give it a go. There's nothing here that should be too strenuous if you refer back to what we've learned through here. But congratulations on learning about transfer learning, one of the most powerful features of deep learning, specifically feature extraction transfer learning. In the next section, we're going to go through transfer learning fine-tuning. So I'll see you there.
Awesome work! You've taken your first real step into the world of deep learning. You've built real models for regression, classification, and computer vision, But this is just the beginning. If you're ready to go deeper and build the kinds of projects that get you noticed by top companies, then it's time to take the rest of Dan's TensorFlow Bootcamp course. Inside, Dan will walk you through advanced topics like NLP, time series forecasting, and fine-tuning models. You'll also work on real-world projects like Food Vision, SkimLit, and BitPredict. Not to mention, it's one of the highest rated online courses for TensorFlow, so I can almost guarantee that you won't be disappointed. Plus, it'll also grant you access to our members-only Discord channel, where you will get priority support from our mentors and our instructors. If you enjoyed this crash course, please drop it a like and leave a comment down below, and share with anyone that might be interested in deep learning as well. Alright, that's it from me, and I look forward to seeing you inside the Zero to Mastery Academy.